Hi, APES students from far and wide. Welcome to the College Board's first virtual lesson for AP Environmental Science. My name is Ms. Fassler, and I teach at Marshall High School in Marshall, Wisconsin. I'm so glad that you decided to join us today. Many of you have probably gotten all of your communication from the College Board or from your teachers about Units 8 and 9, that they are not going to be assessed on the exam. Some of you may have covered some of this material in your courses already. Some of you may not have. So I just wanted to be very clear why the College Board is going ahead and offering some of the content from Units 8 and 9. Colleges and universities came together very quickly and worked with the College Board to offer you a somewhat modified exam and yet still give you your full credit for the coursework that you did in APES. And so we just felt that there should be some kind of agreement that we offered that material to you to give you the full scope and sequence of the course. Sort of piggybacking on that idea, Dr. Sowell and I, the other APES teacher that you're going to see off and on with myself, we got a lot of cool stories to tell from Units 8 and 9 yet that are going to really make some nice connections to the content that you've already learned, provide some review as we're going through those, lots of great career options that we can talk about, and really reinforce the content that you've already had. In addition to that, everything we do, any new content that we introduce, starting with Unit 8 on aquatic and terrestrial pollution, we're always going to tie that back and link it and spiral back to some of the content from Units 1 through 7 that you are going to be assessed on, and we're really going to focus on those science skills and practices. So let's go and jump into a little bit of a warm-up. I know a couple of us have been on for a couple of weeks. We haven't been maybe doing a whole lot. So to kind of get our brains back in gear and working, let's go back to Unit 7 on atmospheric pollution. It's going to be really easy for us to make a connection between what you learned about in that unit on pollution and what I'm going to introduce today in aquatic and terrestrial pollution. And again, really focusing on those science skills and practices. So in Unit 7 on atmospheric pollution, this is one of the really big science practices that we focus on. Number 5, data analysis, analyzing and interpreting quantitative data represented in a table, a chart, or a graph. And you can see that I break that science practice down, and I kind of start out with a pretty simple skill and then scaffold. And by the time I'm done with this practice, I'm going to start by describing a pattern. I'm going to look at relationships among variables for that quantitative graph that I have. And finally, I want to be able to draw some conclusion and relate that back to the content so I can explain that pattern. So let's start off with a graphic representation of some data from atmospheric pollution. This is the kind of graph that you might see even on an FRQ, and they could ask you to use that skill to explain the relationship between the variables, or again, kind of extend that into drawing a conclusion about some bigger environmental process. Many of your teachers perhaps use this technique called I-squared, identify, interpret. You don't have to worry about the formal name for that. It's just a simple strategy that we want to review as I look at quantitative data to make sure I can describe the pattern and find a relationship between the variables. So the first part of that I-squared is identify. What do I see? And I always like to kind of look at the title of the graph and the labels of the X and the Y axis first. So what jumps out at me from that title? I don't know the lines there, but the lines are showing me something about gases. So I know this is going to be air pollution. It's over a city, so that's an urban area, not in a rural area, and it's a smoggy day. So smoggy to me sort of says, oh, there's been a lot of maybe emissions, maybe there's a lot of vehicle traffic. As I look at the x-axis, my independent variable, that's time of day, and I'm starting early in the morning, even before sunrise, and I'm going to early afternoon, looks like I end about 1 o'clock there, and my y-axis, my dependent variable, is concentration in parts per million. So what do I see? Well, I can see that the concentration of all the gases tends to start off low, and all start at the same point, and they all start to increase as I go through over time. I also see that they all tend to reach a peak, and then that concentration tends to come back down again. They don't all go up at the same rate, they don't all peak at the same place, they don't all peak at the same concentration, they don't all peak at the same time, but those are just things that I can observe as I look at that quantitative data. The other part of the I-squared is interpret. What does that mean, all those observations that I just made? Well, remember that science practice, I want to make a connection between those variables. So what I can see is that there's a relationship between time of day and concentration of gases or air pollutants over a city on a smoggy day. Now, let's see how they might ask me something about this on a free response question and getting to that most advanced part of that science skill, being able to draw a conclusion based on this quantitative data. So mentally, I just kind of in my head went through it. I made sense of that graph and I said, okay, here's that relationship. Now, how do I take all of that information that I just processed and use it to draw some kind of conclusion? Well, the fact that these gases are peaking at different times of day, what really is jumping out to me here and what I can explain based on this data, why is it that that concentration of ozone peaks last? And it starts out low and then gets to high concentrations following peak concentrations of hydrocarbons, those VOCs, volatile organic chemicals, and the peak concentrations of NOx. And if you recall from your air pollution unit, those are both what we would call precursors. They are the reactants or ingredients that are necessary for that chemical reaction that creates ground level ozone. So now that we're all kind of warmed up and thinking about science practices and we're all back in the APES group, let's take a look at what we're going to cover in our lesson today. So remember, we're now just going to introduce concepts from Unit 8, aquatic and terrestrial pollution, and I'm going to be covering parts of these 3 different learning targets. Sources of pollution, I'm going to touch on human impacts. Dr. Sowell is going to come back and do a lot more on those tomorrow, and then I'm going to go into thermal pollution. And I've highlighted or bolded the science processes, those skills that we really want to reinforce. So we kind of have 3 objectives for today. Introduce, but spiral back and link new content to the content that you are going to be assessed on the exam. Reinforce those practices and skills that are common and global on the national exam, and then give you a little bit of assessment opportunity to see how you're doing. So let's start off with what you need to know. Our first target is this 8.1 sources of pollution. And again, you've been talking about other sources of pollution throughout the year. This is a very simple target for the most part. It ties in very well to all of our previous learning, because if you look at those essential knowledge statements, it's really defining a point source of pollution comes from a single identifiable point. So in atmospheric pollution, that could have been an emissions pipe from a coal burning power plant. It could be the exhaust or tailpipe from my vehicle. In aquatic pollution, that might be a pipe that is discharging some type of waste directly into an aquatic ecosystem, a coastal area, a lake, or a river. So our goal is to be able to describe an environmental concept and process and distinguish between point and non-point sources of pollution. And then again, that more advanced skill, kind of apply that to explain a model in this case. So point, a single identifiable source, non-point sources of pollution. My knowledge statement here uses the word diffuse. That means kind of diluted, kind of dispersed in low concentration across an area. And it's because of that they're harder to control, because I don't see exactly that pipe where that pollutant is coming from. So let's go into a little bit more detail here. Here's a diagram that shows a very simple example of point and non-point source of pollution. Oh, it's a river in Wisconsin. So one point source of pollution could be if I have human waste being discharged. In my example here, along the base of the river is somebody that has a cabin, and the point source of discharge is this tailpipe that comes out of their bathroom and it's discharging their waste directly into the river. So somebody from the Department of Natural Resources could go and say, okay, I see that there's some human fecal waste coming from your cabin. We are going to need to fine you for that, and you're going to need to come up with an alternative solution. Factory, certainly before the passage of the Clean Water Act, factories would often release industrial effluent. They would discharge waste that could have anything from organic chemicals to heavy metals. And what's really exciting is that we're going to come back to look at some of these specific pollutants. Dr. Sowell is going to do that tomorrow. He's going to talk about wastewater treatment, and I'm going to talk on Friday a little bit about persistent organic chemicals. Again, so you get that really complete picture. Here's what the pollutant is, here's how it gets into the environment, and here's how I as a human then may get exposed to that as well. So let's just do a quick little check and see how this topic may be assessed on an FRQ exam. Identify one point source of pollution and explain how that pollutant that you identified entered the environment. What you want to keep in mind is that that process of explaining, that skill of explaining, that's a verb. I mean, to explain a process requires that I have a verb in there. So I would like, if you've got some scratch paper, use some recycled paper right on the back of the box or something. Why don't you just take a minute and see if you can identify from any unit you've just talked about a point source of pollution and explain how that pollutant entered the environment. So one example that you could have used from atmospheric pollution is particulate matter. Particulate matter is a point source of pollution. It can be discharged. That's my verb to explain that process. It can be discharged into the atmosphere directly from the smokestack of the plant. And you might be able to picture that even from your unit on energy when you look at how during the combustion of coal, I heated water and made steam and turned a turbine and powered a generator. Let's take just a second as we continue moving here to look at those task verbs. In the previous question, you saw the term identify. These are the verbs that are commonly used on free response that give the student an indication of how they're going to answer that question. So identify is the easiest one. Notice that in the description of the identify task verb, I don't have to provide any elaboration or explanation. In the example I used, I simply said a point source of pollution is particulate matter, period. I'm done, point, I got my identify point. The second part of that, the command term, was explain how. And again, we were explaining a process. And so that explain how requires some additional information. We're going to be practicing all of these task verbs a lot throughout the next couple of weeks through units 8 and 9 and when we get into the review. So non-point sources of pollution, if you remember from our original essential knowledge statement, those were the pollutants that were diffuse and they're kind of hard to identify. And here are some examples. This is where we really link back a lot to unit I, where you look at land use. And there's a lot of different like subtopics under land use. You had impacts of urbanization, impacts of feedlots in industrial agriculture, impacts of clear cutting or logging. So it really incorporates this idea of watershed and runoff. Remember, in our definition of non-point, we had that concept that once something happens on the land and that substance can get dissolved in water or snow melts and it carries it down off the land, it's going to ultimately end up in a body of water. Surface water like lakes or rivers or streams, or ultimately could end up in a coastal ecosystem, the Gulf of Mexico. And tomorrow, Dr. Sewell is really going to bring this idea full circle. He's going to come back to non-point pollution and advance that topic a little bit by looking a lot at what goes on in a watershed. So in my image here, oh my God, there's a cow pooping on the watershed. What this is really trying to illustrate is if I had a large CAFO, remember those concentrated animal feeding operations or feedlots, where there'd be a large concentration of animals and then it rained and all of that manure would wash off into the surface water. And again, we're going to talk on Friday about some of the things that are in those pollutants and the human health aspect of that. So they took some of our pictures that we had used, and you have a big blank slide, but just in your head, go back to Unit 5 and think about all those land use practices and how what we do on the land, clear cutting, urbanization, large scale agriculture, could ultimately impact the quality of water through point and non-point sources of pollution. So here's a quick free response prompt to see if you get that idea of non-point source of pollution. And again, it's going to give us an opportunity to practice one of those task verbs, which in this case would be to justify the claim. And so here is the claim that you're going to justify. A neighbor proposes using compost rather than synthetic fertilizer on a garden, stating that synthetic fertilizer would have a negative effect on water quality of local streams. Justify this claim. And in order to justify that, you kind of have to explain a process. I'll give you a minute for that. So here would be a good way to justify that claim by describing that process. So synthetic fertilizers would be more likely to dissolve in rainwater and run off into local streams. The impact of that would be the increased concentration of nitrates. And that's just a really big non-point source of pollution now. Again, that we'll talk about a little bit more. Just kind of a final note on non-point sources of pollution. And it relates back to the Clean Water Act, which you may or may not have talked about. Remember, you already talked probably a little bit earlier in the year about aquatic ecosystems a little bit. So some of this isn't completely new to you. The Clean Water Act, one of our cornerstone federal pieces of environmental legislation in the US, passed in the early 1970s, did an amazing job at controlling point source of pollution because they could go up to that factory and say, oh, you have a tailpipe going into the Ohio River. We're going to find you and you need to come up with a solution to treat that waste and not just discharge it directly into the river. Where we feel the Clean Water Act needs to go next is really addressing non-point sources of runoff. And again, you're going to get a lot on that tomorrow. It's a really exciting area in terms of water quality. Lots of career opportunities in aquatic ecology, fisheries management. So there's just lots of good connections for you to make to other units and skills and practices as well. So let's next go to a couple of those other learning targets that we want to address in our first virtual session today. We're going to touch on part of the essential knowledge from Unit 2, Human Impacts on Ecosystems. Dr. Sowell will come back to that tomorrow. And then we're going to link that into this idea of thermal pollution. So I kind of highlighted in this part of 8.2, there's lots of different essential knowledge statements in 8.2. We're going to focus on one or two of them today. What we're looking at right now is this idea of range of tolerance. That probably sounds a little familiar to you because, oh look, back in 2.4, you did ecological tolerance. It refers to the conditions such as temperature, sunlight, pH that an organism can withstand. Note that all of those are abiotic conditions. So again, we're just reiterating a lot of the content that we already learned about way back in Unit 2 in ecosystems. Look at basic ecological principles. In Unit 8, they come back to that and say, okay, now that we understand that there's this ecological tolerance, what happens when organisms exceed that range of tolerance? Or what happens when they get outside that optimal range of tolerance? And I will point out that part of the definition that I highlighted there, organisms may experience physiological stress, limited growth, or reduced reproduction. And I did highlight the in extreme cases death. I'm going to come back to that in a minute. Well, if this idea of range of tolerance is the span of abiotic conditions over which an organism can survive, one of those key abiotic conditions that's pretty easy for us to understand is temperature. In other words, how do changes in temperature affect the physiological strength of an organism? And that physiological stress, that idea is just a way of saying how healthy is it? Is it able to simply survive, but it's kind of sick? And maybe that change in temperature is impacting metabolic rate or ability of immune system to function or its ability, reproductive capability, or maybe its young aren't as healthy when they're produced in that environment. So we're going to focus on this idea of thermal pollution and relate that to range of tolerance. So here's a very simple range of tolerance graph. You've probably seen ones like this already in your textbook. Remember that learning target about making sense out of a model and being able to explain an ecological concept from apes by looking at a model. So we're going to start by looking at the simple model of range of tolerance to practice that skill. And kind of like that I-square technique that I did, I want to break down what the model is showing me, just like I broke down what that quantitative graph was showing. So I've got temperature. There's my abiotic condition. The term performance, that's about how well my organism is doing. So I can see that across this is a very generic, simple model to start with. Across this range of temperatures, there's an optimal range. That optimal range of tolerance over which organisms are not just going to survive, but they individually as an organism or even as a species, that whole population of fish in a stream, they're not just going to survive, they're going to grow. They're going to be pretty healthy. And not only are they going to grow, but they're going to reproduce. And so this is that optimal range so that they're really healthy and they have a high performance. They're not under stress because the temperature got too high or too cold. Too hot or too cold. Notice as I move either hotter or colder away from there, I get into the zone where, they're surviving and they're growing, but their reproductive capacity has been greatly reduced. Maybe survivorship of offspring has been reduced. And finally, I get out to these extremes. They haven't died yet, but all they're doing is surviving, and their numbers are probably quite a bit lower. So that's a pretty straightforward graph to visualize, a model to visualize. Now let's make that connection to why do we care if the temperature gets, in this case, too warm. So when we talk about thermal pollution, it's one of those things where I don't add an actual pollutant to the water. I'm not adding mercury, or I'm not adding livestock waste that could have high levels of nitrates or coliform bacteria. I am simply discharging, and it's usually a point source of discharge from an energy plant. So if you think back to your energy unit, when you had a coal burning power plant or you had a nuclear power plant that was fissioning atoms of uranium-234, remember they all needed water as a coolant. Picture like the big sloping cooling towers in a nuclear power plant, and I've got to heat burn. I fission those atoms or burn that coal, I heat water, I make steam, I turn a turbine, and I power a generator. So if that plant, or it could be an industrial process as well, if that plant releases water, hot or warm water, above the normal water temperature of the local stream, for example, that's what we call thermal pollution. And the big problem with that is that it affects yet another abiotic factor of an aquatic ecosystem, in this case dissolved oxygen. Now, understand that if you want to dig in more to thermal pollution, there are certain other direct effect on species, thermal shock, changes in metabolic rate for cold-blooded organisms, but the connection we're going to take a minute and make here is how it influences gas solubility. So if you remember, when I increase the temperature, those oxygen molecules are dissolved in water, and that's how aquatic organisms get their oxygen. They don't have like a little alveoli in their lungs where there's a gas exchange like we have. That water passes over their gills, and that dissolved gas diffuses directly into their bloodstream. So if the water temperature gets too warm, I lower the ability of that water solution to hold dissolved oxygen gas. Think of that, those warm water molecules are moving around with all kinds of kinetic energy, and those oxygen molecules are jumping out of solution. The analogy would be if you open a can of soda, gas dissolved in the soda is carbon dioxide, the fizziness of it. If you put it in the fridge, it's going to stay fizzy because that carbon dioxide is going to stay in solution longer if it is cold than if you leave it on the counter where it's going to get warm. So let's go through and do an example using range of tolerance. I have a diagram here. There's a few more labels on it, and we're going to practice that skill again. Describe how a population of steelhead trout will be impacted by an increase in the average temperature of the stream in which they live. We got a bunch of trout swimming around there. You have noticed I'm wearing my fishing jacket. We're still just wrapping up ice fishing in Wisconsin, but pretty soon the ice will melt, and then we'll be out doing just regular fishing on the lakes. So let's go back to that I-square technique we used early and take a minute to make sense of the graph and see if you can jot down a response. Describe how a population of steelhead trout will be impacted by an increase in temperature. So one of the things you could have said there in your describe how is that if the average temperature increases, it will be outside the range of tolerance for some organisms that live there. Boy, what a powerful term to have in my vocabulary, because anytime I change an abiotic condition, I don't care if I'm on land or in the water, if I alter any abiotic condition, pH, salinity, temperature, dissolved oxygen, it may be outside the range of tolerance for whatever species or organism is living there. And so when that temperature is outside the range of tolerance, the trout are not going to be as successful. They will be experiencing physiological stress. They won't grow and reproduce as successfully. So there's a lot of different ways I can say once I'm outside the range of tolerance, here I'm describing how they are impacted in a nice, concise way. Not really a misconception, but one of the points I want to make in terms of reading exams, a lot of times, and this is just a broad concept, and to be honest, it really relates a lot to atmospheric pollution and the human health impacts of atmospheric pollution. You want to be careful about always saying that it kills something. I understand that our essential knowledge statement, it said there's physiological stress or even death, but if the specific question that you're addressing, for example, if I look back on my steelhead trout here, I don't know off the top of my head what the range of tolerance is for a steelhead trout, and I don't know if 9 degrees is necessarily going to kill them. According to this, that's the zone of intolerance. They're probably not living there, but these labels maybe wouldn't have been on a diagram. So you want to be careful, and we want to make sure we have that description that when outside the range of tolerance, those organisms, they don't grow and reproduce. Or those I think are a pretty easy way for you to remember what happens when we get outside the optimal range, which in the case of the steelhead trout is between 13 and 21 degrees Celsius. So again, just be careful that you're not killing them, because depending on the specific situation, it may not have been an extreme enough condition to actually kill them. So let's do a quick check for understanding to see how you feel about range of tolerance. Here's an example of a release exam question on range of tolerance, and I'm going to give you a couple of minutes again to try to jot this down. Just skip this section here about hydrogen ion concentration. We'll just read the background information, and then you can answer the first half of A and prompt B. The diagram represents the pH ranges, my abiotic condition, of selected aquatic organisms exist. The solid figures represent pH organism, the pH ranges at which the organism will thrive. Notice that you have sometimes you're shown sort of a shaded figure where the conditions are less favorable, but they survive. And if there is no symbol there at all, it simply means they're beyond the range of tolerance. So we want you to go ahead and try to answer that question. How are we doing? All right, let's check to see how you did. So the brook trout can survive, or thrive, in a pH range from 5.5 to 7. Notice that the key part there was thrive, and so I had to kind of make sense of my diagram a little bit, the shaded versus the unshaded. And then the rainbow trout would be the best indicator. They have a pretty narrow range of tolerance. Notice that once it got a little bit below a pH of 6, or that pH of 5.8 that I was looking at, my brook trout were there, but they weren't thriving. They were not able to grow and reproduce. They were under physiological stress. So again, in bringing to closure some ideas about this range of tolerance, it's a very broadly applied concept to a lot of different abiotic conditions, and it allows me to describe a connection from the ecology unit between biotic and abiotic components of the ecosystem. So let's look at an AP exam practice question. question. Oh, wait a minute. There's one last little learning target from section 8.2 that I wanted to mention, and that's on oil spills. If we were assessing Unit 8, we go into a lot more detail on oil spills. I just want to present some introductory information here so that we can make sure and link it back to some prior content. You probably remember from your energy unit, one of the main focuses in the energy unit was taking all these different resources or forms of energy and saying, all right, how do we use them? What kind of energy do we get from them? But really the big thing is what are the pros and cons? What's the advantage and disadvantage of different energy resources? And certainly one big disadvantage of using petroleum as an energy resource is that it can lead to oil spills. So depending on how I transport that oil, I can transport that oil in a pipeline, overland. I can transport that oil under the ground in a pipeline. I can transport that oil in an oil tanker. So I can load it up, that oil up from an offshore platform, load it onto a tanker, and transport that oil via a tanker. So they hold a lot of oil. We transport an amazing amount of oil, millions of barrels a day, used just in the United States alone. And there are many potentials for that oil spill to happen. So I have just a cute little video here for a second on some of the problems that oil spills cause.
Have these penguins been yarn bombed? Nope, it's just the most adorable knitwear in the world that wildlife advocates say can actually save the birds' lives. I'm Jen Markham on Buzz 60. Penguins usually don't need a sweater on a chilly day. They live in the coldest environments on the planet. Every day is a chilly day. But wildlife advocates say when a penguin is caught in an oil spill, the oil can separate and tangle their feathers, compromising their protective heating and blur layer. Even worse, the penguins can end up eating the oil when they try to clean it off their feathers. That's why the Penguin Foundation started a program called Knits for Nature, asking volunteers to knit sweaters for the penguins on Phillip Island, Australia, to keep them warm and protected. The group provides a knitting pattern to download so volunteers know the size, and they can hold a yearly contest with.
Oh, so that was pretty cute. Seeing the little penguins with their sweaters. So one of the benefits of the sweaters was, again, so that they stay warm because the oil interferes with their insulating capability of their feathers or their fur. And one of the biggest issues, however, with the oil spills on marine organisms is that they ingest that oil when they're preening themselves. And that's a big idea we're going to come back to on Friday when we look at how wildlife and humans get exposed to some of those persistent organic chemicals like we find in that oil, in the hydrocarbons. So last chance then to do a little bit of assessment. The last learning target that, if you remember from the beginning, that we were going to address was doing some kind of mathematical routine. And I started us off with a couple easy ones. Dr. Sowell and I will give you lots of opportunity to practice different kind of mathematical routines. But here again is some quantitative data from a national exam question showing the amount of oil released during different oil spills. Remember, I'm going to break down what this graph is showing me. They're showing me both the low estimate and the darker shaded region high estimate. It's oil spilled in millions of gallons. And that's an area where a lot of people are going to make a mistake. So I'm going to give you a chance to answer questions A and B. So let's see how you did on that map. In the first one, what I needed to do was add together for the Deepwater Horizon. That's an oil spill that some of you actually may have heard of. I had to add both of those two values together. Here's the one tricky thing in an area where you may have made a mistake is if you only put 340, you would have gotten it wrong. Remember, that's the benefit of looking at the labels of that X and Y axis to begin with. This is not just 200 barrels, it is 200 million barrels. So that's an area where they might snag you a little bit. And then in question number 2, a lot of times I tell my students when they're struggling with a math problem, sketch a little picture and try to visualize what the problem is asking you to calculate. So what they're saying is the total, like the coastline of the Gulf of Mexico that was impacted with oil, was 3,540 miles. Oh my gosh, it's hard to even imagine, isn't it? And understand that the Deepwater Horizon was an offshore oil platform. It was miles and miles off the coastline. So all of that oil through the wave and action of waves was brought into the coastal ecosystem. Of that total coastline, that's the total length of the coastline. 1,313 miles of it were impacted by oil. So that is just, it's not a percent change problem. It's just a percent problem, part over the whole times 100. So just a quick debrief. Let's look back at those objectives we had from the beginning of the lesson. We introduced some new content, but make sure we linked it back and reinforce some of the content that we spiraled back to from the first 7 units. We did hopefully a really good job of reinforcing some of those skills and practices that are global for our exam, and then gave you a little bit of guided instruction for some practice on that. Coming tomorrow, Dr. Sowell is going to talk about the environmental effects of different pollutants, and he's going to go back and review a lot of different kinds of aquatic ecosystems. Should be really exciting. I'll see you again on Friday to talk about persistent organic pollutants and endocrine disruptors. Thank you so much for watching. Have a fabulous rest of your day. Stay safe, all of you in the APES community. Bye.
Hi everybody, welcome to our second virtual lesson for AP Environmental Science. My name is Dr. Scott Sowell and I teach APES at Darnell Cookman Middle High School in Jacksonville, Florida. So just as a little warm up to kind of get our brains back into gear here, I'm going to take a look at a question or a topic from Ms. Fassler's previous lesson, the first virtual lesson on point versus non-point. So take a look at this multiple choice question and I'll give you 30 seconds to answer. All right, so the answer was D. So we're looking for both a point and a non-point. Unfortunately, A, both of them were point sources, and B and C were both non-point sources. So just to kind of get your brain thinking again about point versus non-point, Ms. Fassler talked about yesterday. So where are we going today? We're going to be looking at 8.4, human impacts on wetlands, and 8.5 on eutrophication. I know the title of this slide really focuses on 8.2, human impact. We are going to do that. We're just going to go into a little bit more detail, specifically on wetlands and also on eutrophication. And through both of those topics, we're going to look at 2 skills. Practice number 7, environmental solutions, so providing potential solutions to environmental problems, as well as the role visual representation plays, not only in your understanding of environmental science concepts, but in communicating those ideas. Top little right thing here that says AP exam is a good reminder for me to clarify something. So you may have heard from the College Board or your teacher or from each other that the APES exam this year, the AP exam will only cover the first 7 units. So you may ask, well, why are you looking at unit 8 and 9? There are very important topics within 8 and 9 that are still very useful and critical for you to know, especially in terms of what the college expects for you to know if you're getting credit for. So while the first 7 are what you're being tested on, 8 and 9 will not be. However, there's plenty of things that we're going to loop back to in the first 7 units through our work with units 8 and 9. And once we get to 8 and 9, then we'll start reviewing 1 through 7. All right, so by the end of this lesson, we're going to see how well you can do these 4 things. So right now, as I go through them, just think, how comfortable are you with it? So the first one, could you explain the impacts of specific activities on aquatic ecosystems, a wetland, or a river? Could you identify and describe what kinds of scientific data to collect to support your explanation? Could you propose a solution to whatever issue you identify? And then could you effectively use visual representations of science content during that process? So we'll see how comfortable you feel with these 4 things at the end of the lesson. So you'll notice that in these questions, I bulleted the task verbs. So these are ones that you're going to see on the FRQs. So calculate, describe, explain, identify, justify, make a claim, and propose a solution. These words are not used lightly. They have real meaning. So your answer and the type of answer and the length of your answer and the structure of your answer will change based on the task verbs. So I would recommend really getting to know them. And what we're going to focus on a lot today is propose a solution, that very bottom one, because that's a specific paragraph. All right, so let's get started. So this is 8.4, human impacts on wetlands and mangroves. And through this, we are again going to look at the practice number 7, and specifically 7B, describe potential responses or approaches. So in order to get to this first section on wetlands and mangroves, you should be able to explain the impacts of human activity on those 2 wetlands. To get there, we're going to describe what wetland is. We're going to talk about wetlands, including mangrove forest. We're going to identify some human action with the ecosystem. Then we'll look at the effects, both economic and environmental, of those actions. And then finally, we'll look at some solutions. So just looping back to prior units, there is some content that we're going to talk about today that you might want to review. And then by doing this lesson, it'll help you review as well. So for example, Unit 1, topic aquatic biomes, nitrogen cycle, and phosphorus cycle. We all love the biogeochemical cycles, and they are definitely not something we learn and don't use the rest of the course. Those cycles continually loop back over and over again, and in today's session, we'll be looking at both of those. So let's just define wetlands. A wetland is any part or any area where water covers the soil either part or all the time. They can look very different depending on where they are. They might be coastal, they might be inland, therefore they may have different salinity levels, freshwater, saltwater, brackish, so they can look differently, but they're all going to have that characteristic of the soil being covered by water either part or all of them. Two big categories of wetlands. There are different categories. There's other classifications, but the two I think are worthy of looking at today are marshes, which are dominated by grasses, and swamps, which are dominated by trees. Both wetlands are two different types of dominant vegetation. And in particular, one type of swamp is a mangrove forest. This is a type of coastal wetland. It's got these very unique mangrove trees that salt tolerant, salt loving, and they've got these very characteristic finger-like crop roots that grab onto the soil. So clearly, it would be a great thing to reduce soil erosion. Rich biodiversity, lots of habitats for different species. Species richness and productivity would be high here. There's a large one in South Florida, here where I am. The largest one is in Asia, but we do have some in the United States. All right, why do we care? Why do we care about these wetlands? So we have some ecological services that are really, really important. First of all, water filtration and purification. So I want you to kind of imagine over here on the left-hand side, there's a flowing river that is going to eventually empty into this large body of water, like an ocean over here. But in between this fast-flowing water and this other body of water, we've got this marsh right here. And this marsh almost acts like a speed bump and slows that water down. And as the water slows down, some of the sediment can settle out, so the water is a little bit cleaner. The second way it does this is look at all this vegetation. All of these grasses are assimilating and absorbing nitrogen and phosphorus. So by the water simply passing through this wetland on its way out, it is reducing turbidity. Sediments are coming out. It's also reducing the nutrient load, the amount of nitrates and phosphate in the water. There's some similarities here between what actually happens in wastewater treatment plants. So next year when we talk about wastewater treatment plants, things that humans have built to clean our wastewater, think about some parallels with what the natural world already does with wetlands. So something kind of cool to think about for next unit. So clearly here's our nitrogen cycle. We've got the good old nitrogen cycle, and specifically we're talking about assimilation. Plant assimilating or taking out nitrate, phosphate, all the eight. That's what I was trying to remember. But this is a great example of a visual representation. We've got all these little pieces of art that we need to figure out. What is rhizobium play? What is emulsification? What is denitrifying bacteria? All the little players and components. And it tells a story. There's a utility to this model, to the visual representation. And you're going to see visual representation more than likely on the exam. So let's take a look at another benefit. So flood protection. So not only does this wetland act like a speed bump to slow the water down, it also acts like a giant sponge, especially for storm surge, things like hurricanes. So the picture on the left is a big storm surge, big wave crashing right into the land, pretty disruptive. But imagine if that wave had to travel through this wetland before it reached shore. So it has a really good function for us. And then clearly, it's got a large habitat, or maybe a wide variety of habitats, lots of species richness for both terrestrial and aquatic, alligators and swamp. So that's what wetlands are. Pretty simple to understand. Their benefits are many. And then we come along. So we definitely need to understand that anthropogenic or human caused wetland. So first of all, we'll talk about commercial development. If I build where a wetland was, the wetland is no more. Pretty straightforward. So commercial development and buildings and roads and shopping malls and parking lots, all of that stuff. We mentioned before that there's a great biodiversity in wetlands, and so overfishing might disrupt dramatically those food webs. And if we see species richness start to fall away and we have much more of an unstable food web, the overall sustainability or the equilibrium or the resistance and resilience of that ecosystem could go down. And of course, like the picture says here, a dam. A dam is clearly going to disrupt the natural flow of the water and therefore probably alter the locations of wetlands. It might destroy wetlands in some places, or even maybe above the dam in the reservoir create additional wetlands, but it's definitely a threat to natural distribution. And finally, this is the one that we're going to talk mainly about today, is pollutant from agriculture and industrial waste. If you'll remember from yesterday, Ms. Fassler talked about non-point source pollution, so that agricultural runoff, those inorganic fertilizers becoming soluble in rainwater, and as that groundwater moves and the surface water moves, it's going to drag those inorganic nutrients to a different location, and that surface water can run off and eventually make it into bodies of water. So if we understand what wetlands are, we see some of the threat. Now let's think about solutions. So I really like the way that this practice is laid out. The overall practice says propose and justify solution. You can notice it goes in levels of complexity. The first part, 7A, what's the problem? You got to understand the problem before you can do anything about it. And then 7B says, okay, I've got this problem. Let's think of some possible ideas, right? And then 7C and 7D say, of those possible solutions, what kind of advantages, disadvantages, unintended consequences, pros and cons? How do those things help you make your decision, as well as what empirical scientific data did you collect to help you make that decision? And then towards 7E and 7F is you finally make that decision and then justify it. So it's a really beautiful way of describing environmental solutions, which oftentimes we should think of as there's a problem, but here's an idea. That's very different. We're not just coming up with an idea. We're trying to formulate the best solution possible. Here's a common mistake though when talking about environmental solutions. Common mistake is to provide a solution that is simply unrealistic. So on an FRQ, if you're asked to talk about solutions, make sure it's realistic, something that could actually happen. Here's an example. And this example, I apologize, is about wetlands. It just happens to come from last year's exam. So it says one reason that people visit national parks is to view scenery. Visibility at the four part in the graph has been reduced over time, so that by 2015, the visibility was an average of 70 miles less than historical visibility. Regional air pollution sources are commonly located over 100 miles away from national parks. We've got this situation where the visibility in park has gone dramatically down. And the first part of the question asks you to identify certain pollutants that might be involved in this, whether they're primary, secondary. But then the subsequent question says, discuss two specific actions that the state or federal government could take or encourage to further improve the visibility in the Great Smoky Mountains National Park. So if you look at the scoring guideline for the question, it says this is for 2 points. It's asking for two specific actions. 1 point each for each correct and realistic discussion. So your discussion, your solutions have to be realistic. So for example, you could require or offer incentives for companies to reduce their emissions, limit vehicle traffic in park. The last one, limit incineration practices or prohibit campfires. All of those are realistic. In the chief reader report, where the readers from the grading of the FRQs kind of talk about common misconceptions, they say about this part that strategies such as move factories to further than 100 miles from the park or close down all the factories in the area did not earn points because they were not realistic. So just keep that in mind as you look at solutions for FRQs. All right, let's just do a quick check for understanding. I'm going to give you another multiple choice question. So it says a beach community was recently negatively affected by a hurricane. Community leaders are looking for a potential solution to prevent damage from future hurricanes. Below is a list of their concerns as well as how important each issue is to the community. So take 30 seconds, look through the community concern, and answer this question. Which of the following solutions would best address the issues of greatest concern? All right, so hopefully you picked planting the mangrove forest. When I first read this question, the thing that stood out to me was the importance of roosting bird species, and clearly mangrove forest would provide that. So here's another example. This is the 2003 FRQ question number 3. I'm not going to ask you to answer this one. I just want to point out that based on what we just learned, you would probably score very well in this FRQ. I've underlined the capper for you. I want to pay close attention to this one. Discuss 2 roles that coastal wetlands play that are ecologically important and 2 roles that they play that are economically important. And it says, hey, what have we done? Describe or identify and explain 3 ways in which humans have had a negative impact. And then finally, what's some kind of proposal or solution? So there's the same model that we just did. We identified why ecosystem or wetlands were important. What have we done to them, and what might we do to root out? Quick reminder: if an FRQ asks you to identify 2 things, then the first 2 things are the only things that will be scored. For example, if I said right now, name 2 fruit, and you say elephant, chicken, apple, and banana, you score 0 points because the first 2 things you said were incorrect. So be sure that you are very clear in the direction saying what you should write. And remember, it's not about what you meant, it's about what you wrote. So to strengthen your understanding a little bit about wetlands, I want to show you a clip from Dr. Silliman, and he is working in a coastal salt marsh. The video is a couple minutes long, maybe 2 minutes long. We're not going to watch all of it, just the first minute or so that you can get some visuals of a wetland. He's also going to talk about some of their
When I walk into the marsh, one of the first things that I notice is this vast intertidal grassland of hugely productive vegetation. Salt marshes are found in protected coastal waters and temperate zones all over the world. Salt marshes are world famous for being among the most productive ecosystems in the world. Their productivity rivals that of the plant material in tropical rainforest and Amazon coral reefs. Marshes are very important for humans. They're pollution filters. They also protect our shorelines from erosion. They're really important for fisheries production. And because of those important services, people are not only interested in keeping the marshes around that are here, conserving them, but putting more out there. I've been studying salt marshes for over 20 years to understand how they work. I want to know what forces keep them healthy and what we can do to maintain them.
So I would recommend watching the rest of that clip. It's a great clip. It's a fantastic review of food webs and trophic cascade. And it's also an excellent example of good experimental design. Mr. Sullivan is very explicit about how he sets up his experiment, his experimental groups, his control group. So again, a great video, not just to check your understanding of wetland, but also food webs, trophic cascade, and kernels. If you have not used them before, I wanted to introduce you to data nuggets. They're a brilliant resource. I use them a lot with my students. If you haven't used them before, here's a quick summary. It's a brief description of a scientific study, and it gives you some data. And then you have to answer a question based on that data. You typically generate a graph, and you fill out a claim, evidence, reason, if you're familiar with DER. If not, it's just a way to answer a testable question using the scientific data provided to you. Well, there's lots of data nuggets out there, but there's one in particular called Marsh Makeover, in which Dr. Bowen looked at a marsh ecosystem that's undergoing restoration, so experiencing a solution. Someone decided this is what we're going to do to improve the wetland. And they're doing it. Her job is to go in and say, well, how well is this working? So she sets up an experiment in which she studies the response to the native grasses from that restoration. So it's a cool review. I recommend it. And it also touches a lot on the carbon cycle, on the carbon storage. All right, that's 8.4. Let's move more into 8.5 now. A little bit more focused on a particular phenomenon called eutrophication. And as we go through this, I'm going to try to focus a lot on visual representation. Our course really relies on diagrams and images and model things to help us understand the earth systems and how we affect. So for example, this is coming from the College Board. So at the bottom it says visual representations are tools for learning, exploring scientific concept and idea. It lists a lot of them. Just think about the soil triangle. We all look at the soil triangle when we're in our soil and agriculture conversations, and that's a great visual representation. It has a story to tell. It's not just how much silt was in my soil sample. You take that and you use the story to talk about agricultural amendments you might give to a soil, or what type of soil might work best to line the bottom of a landfill. So those visual representations individually, you need to understand them, but you also need to be able to use them in other contexts. So by the end of this section, you should be able to explain the environmental effects of excessive use of fertilizer on aquatic ecosystems. So in order to get you to that understanding, we're first going to talk about systems where that problem is non-existent. So that's oligotrophic waterways. Oligotrophic waterways do not have excessive fertilizer being dumped into them. So we're studying that first. Then we'll talk about how those fertilizers get into the system, and you should probably already start thinking about those non-point sources, agricultural runoff, inorganic fertilizers, the we talked about yesterday. And then once those fertilizers get in there, we now have a system that is eutrophic. So we're going to go from oligotrophic to eutrophic. And then we're going to talk about what are the effects of that on not only the environment but the economy. And finally, we'll again look at how visual representation helps to do that. So let's do oligotrophic first. This is a pretty clear example. So a typical body that's oligotrophic is low nutrient level, so not a lot of nitrate, not a lot of phosphate. Low turbidity. Here's a good word to remember. Remember that turbidity means cloudiness. So if I had a pure glass of water, drinking water, the turbidity would be low. But my tea here is kind of cloudy, and that has higher turbidity. So an oligotrophic body of water, low nutrient, low turbidity, and high dissolved oxygen, IDO, because there's a stable amount of, or a high amount of dissolved oxygen, to maintain a stable population of fish. And finally, a characteristic is that there's not a lot of algae growth. That'll become apparent when we look at the next thing, eutrophic. And eutrophic bodies of water are the opposite. So they have high nutrient level. Again, start thinking about how those nutrients have gotten there. More cloudy, more turbidity. The DO is lower, and therefore sometimes cannot sustain healthy fish population. And finally, as you can see in the picture, lots of algae. Usually we have a lot of algae growth. Now, I need to pause here and mention that this can happen naturally. There's natural eutrophication. Bodies of water can become eutrophic over a long period of time. And that's completely natural and normal. What we're more concerned about in environmental science is cultural eutrophication. When humans do this process very quickly and intensely, so that the effects are much more dramatic. Just as a little side note, this is a great tool to measure turbidity called a Secchi disk. And so if I have really turbid water, like the water on the right hand side, if I lower this disk down, you'll notice I start to lose it. If this water is really clear, I can lower this disk almost all the way to the bottom and still see the black and the white. So a Secchi disk is a great way to measure turbidity by simply lowering the rope down and measuring the distance down before you lose sight of the black and white. So a great physical test for the water. So here's a good visual image. So I want you to look at the title first. So this is eutrophic and hypoxic coastal area. Hypoxic means low oxygen. So take 15 seconds, stare at this visual image, and maybe start to think what stories it's trying to tell you. When I look at this, I see obviously it's on the coast. This is coastal eutrophication, but it's also more apparent in places with high human population. I don't see a lot in Greenland. So let's zoom in a little bit on just the United States. Huge amount of eutrophication and hypoxic conditions along the eastern coast, particularly Florida. You can barely see my state from all the top. But we're going to look at one particular place where eutrophication has occurred in the Gulf of Mexico. And it's occurred so predominantly and consistently and profoundly that it's become quite famous as a dead zone. So I'm going to show you a clip from a Miami news channel, and they're going to do a great job at talking not just about the mechanics of what's happening in eutrophication, but also what are the economic and environmental consequences. So as we watch, try to know what causes eutrophication and what are the effects.
A man-made phenomenon is threatening marine life in the Gulf of Mexico. The largest dead zone ever recorded in the U.S. has appeared at the mouth of the Mississippi River. Scientists say it's primarily caused by fertilizer and sewage that wash off farmland. The runoff eventually makes its way to the sea, where it feeds algae blooms and bacteria that sucks out all the oxygen of the water. CBS News correspondent Jeff Flores in Louisiana with how the dead zone is impacting one of the largest seafood industries in the country.
Underwater video we recorded yesterday afternoon shows the transition from life to death as green fades to black. It becomes so dark, divers need flashlights to find their way around. Down here, there is almost no oxygen in the water, and this void stretches over an enormous portion of the Gulf.
This is the largest one we've ever measured and the second largest human-caused dead zone in the ocean.
Nancy Rebelay is the nation's foremost expert on dead zones. She's been measuring oxygen levels in the Gulf since 1985.
It's a feature that's large, it's not getting smaller, and attempts to manage the nutrients, nitrogen, particularly from the Mississippi River, are not having an effect on reducing the size.
Dead zones happen when agricultural runoff sends nitrogen-rich fertilizer downstream into the sea. The fertilizer feeds harmful amounts of algae at the surface that eventually die and sink to the bottom. Bacteria feast on the dead algae, removing oxygen from the water, and fish, crabs, and shrimp are forced to leave or suffocate and die.
The solution lies upstream in the watershed with better agricultural management practices, a switch to crops that have deeper roots and don't need as much fertilizer, and are still just as profitable as corn.
The water we watched them measure yesterday has less than half the oxygen needed to support basic fish life. It's almost like a different planet.
It's very good, yeah. If you're a scuba diver, you're used to having fish swimming all around you. From 30 to 60 feet, you won't see any fish. Nothing.
These species of shrimp are not there like they used to be.
O'Neill John Sabin has been fishing these waters more than 40 years. From a fishing perspective, you're talking about smaller shrimp or no shrimp at all.
Correct.
A study led by Duke University published this year found that dead zones in the Gulf do slow shrimp growth, resulting in higher prices for larger shrimp.
Do you see this issue getting better anytime soon?
Well, I wish it would. I really do wish it would.
The EPA has set up a task force to look at dead zones. They're hoping to reduce nutrient-rich runoff by 20% by 2025. In Dulac, Louisiana, Jeff Lohr, CBS News.
So hopefully you heard in there some terms that you're familiar with: agricultural runoff, dissolved oxygen, nitrates. So let's continue on. So again, this Gulf of Mexico dead zone is really a result of this Mississippi watershed right above it. So remember the word watershed. It's such an important term to understanding how surface water and groundwater move across the land. So all of the water or all of the agriculture that goes on within the Mississippi watershed, if there's any nutrient runoff, any of that non-point source runoff of inorganic fertilizer will eventually make its way down into the Gulf of Mexico when we get there. So the next thing I'm going to show you is a kind of a visual representation of eutrophication that I put together for myself to better understand it. I've used it with my students. But now that you've heard it in the video in the newsletter, now take a look at my version and see how well they jot together. So we're going to start with wastewater relief. So if we think about CAFOs, concentrated animal feeding operations, or point source pollution coming from maybe a wastewater treatment plant, we're looking at wastewater entering the water. Well, as soon as something like that hits the water, the first thing that's going to happen is it's going to start being decomposed. So before this wastewater release happened, there's a few decomposers are naturally there. Decomposers are everywhere. All of a sudden, this wastewater comes in, and now there's just so much food available for these decomposers that their population skyrockets. There's a huge explosion in the population of these decomposers. Well, decomposers need oxygen. So before the wastewater, there's only a little bit of a demand for oxygen, and the amount of oxygen in the water is really hot. And all of a sudden, this huge explosion of decomposers is demanding all of that oxygen, and the dissolved oxygen starts to go down. One of the byproducts of these decomposers is nitrogen, phosphorus. Well, as we know from our biogeochemical cycles, that is easily assimilated in plants. And so now we get this notion of eutrophication. The pollution is fertilizer, is nutrient. So this huge influx of nutrient fertilizes the algae. It's food for the algae. And now we get a huge explosion of algae population. We call that an algae bloom. So just imagine if I have a cornfield and I want to make that corn grow really, really strong, I'm going to add fertilizer. And same thing what's happening here in the water. Fertilizer for the algae. So now we have a huge explosion of algae. So the water's going to get more turbid and even block sunlight from lower submerged vegetation. But here's the next problem sequence. We also have agricultural runoff adding even more nitrates and phosphates in the water. However, algae don't live long. So eventually they're going to die. So this massive explosion is all going to die and become even more food for decomposers. We're going to suck more oxygen out of the water. And now we have this condition and a dead zone where we might have a fish kill. Sometimes the fish can swim away, maybe, but if you're an organism that fits in place, maybe you can't. Remember from yesterday's discussion with Ms. Fassler, range of tolerance. So each organism has a range of tolerance for lots of different abiotic conditions. Dissolved oxygen is one of those. So there's a range in which the amount of dissolved oxygen is okay for me to live. But if it gets any lower, I start to not perform as well as I might. If it gets too low, I can't live there. So range of tolerance is a good thing to bring back from yesterday and today, or from the last lesson today. So you've heard it once from the news, you've heard it once from my diagram. Here's the last iteration of it, a little 1 minute summary.
What is eutrophication? It's a problem that should matter to you, whether you live near the ocean or not. That's because it begins wherever people live and ends with damage to resources we all use and enjoy. It all starts when nutrients get into lakes and oceans. Remember, what's waste to humans can be food to plants and other creatures. Nutrients need algae, like they do other plants. Algae grows and blocks sunlight. Plants die without sunlight. Eventually, the algae dies too. Bacteria digest the dead plants, using up remaining oxygen and giving off carbon dioxide. If they can't swim away, fish and other wildlife become unhealthy or die without oxygen. But it doesn't have to be this way. Protecting marine resources starts with sound agricultural and waste management practices.
The video ends with pointing to the two things that we just talked about, agricultural runoff as well as wastewater management or wastewater relief. But I do want to just put the ball in your court a little bit, or maybe in a little bit more local context. Think about someone who might have a large front yard and they're using fertilizer on that yard. Some of that fertilizer becomes soluble with rainwater, runs off into a retention pond, and now we have an algae bloom. Or imagine a big golf course nearby where they can maintain that lush monoculture crop of grass. That's going to require fertilizer. So while we can think of agriculture and wastewater, we also need to think of personal, residential, commercial causes. All right, so now let's link some stuff together. So I want you to remember, again, Ms. Fassler the other day talking about point versus non point. Now I want you to consider two different bodies of water. So you've got this small retention pond down here with a non-flowing body of water, and then you've got the fast-flowing stream. What I'd like you to do is take 37.5 seconds and think, how might wastewater pollution from a point source affect these two waterways differently? Just take a second. So you may be starting to think about, well, there must be something about flowing versus non-flowing. I kind of made that pretty explicit. So let's take a look. So we're going to use a visual representation to do that. And just like the last practice, the practice goes from simple to complex. When we look at a visual representation, a soil triangle, a graph, food web, any kind of model, first thing we have to do is take out the player. What are the characteristics of that visual representation? Then second, how are they related? Are there two variables that are related? Are there two organisms that are related? Are there cause and effect? And then we can tell the story of what that visual is trying to tell us. One of the mistakes we often make, and I'm guilty of this too, is as soon as I see an image, I jump right down to that third thing and try to figure out what it's trying to tell me. And I should slow down just a little bit and focus on who the players, how the players related, and then what we're trying to tell. So take that set of skills to this diagram. On a piece of paper, I'd love for you to just jot down what you see and what it might mean. So on a piece of paper, I'll give you 1 minute to jot some ideas down. Okay, I lied. I'm going to give you 30 seconds. So this is the oxygen sag curve. Oxygen sag curve. This is also a learning objective within AP Environmental Science, and it really just talks about some of the things that we mentioned before, but now in more of a flowing stream or river. So the first part of this skill is to identify the player. So because this looks like a graph, you should notice we've got two lines that are changing. We've got the demand for oxygen and the actual supply of oxygen. When the demand of oxygen was low, we have oxygen in the water. But all of a sudden, we have this point source pollution, this wastewater, huge bloom or explosion of decomposer that are demanding a ton of oxygen and sucking it out of the system. Now, you'll notice though, it starts to recover. Now, obviously, the degree of recovery will depend on how long it goes on and how intensely, but you'll notice that the dissolved oxygen and the demand for the oxygen kind of go back toward normal later on. Oxygen sag curve, great visual. So could we use this visual to help us understand other contexts? So hint, we'll come back to this a little later on for FRQ. So here's an example of a visual image that was on the 2018 exam. So food web, a great example of a visual representation. The first thing that you are asked to do on that FRQ is to identify the player, pieces in the part, what's going on there. So who's the primary producer, who's the consumer, who's the secondary consumer? And then, not surprisingly, the next question said, are they related? These arrows mean. So again, that really helps you to understand the story you're trying to tell if you understand the characters involved and how they're related. So let's summarize. We had two goals, 8, 4, and 8, 5, and we wanted to focus on solution and visual representation. Hopefully we've done that. Now remember there's 4 things I asked you to think about. Let's revisit those and see if you feel maybe a little bit more comfortable doing some of them. Could you explain the impacts of specific human activities on aquatic ecosystems such as a wetland or river? Could you identify and describe what kinds of scientific data to collect to support reclamation, maybe something like turbidity or salt oxygen or nitrate or maybe even species restriction? Could you propose a solution to local stakeholders? And then could you use visual representations within the conversations or decision-making process? I do want to pause for a second and talk about a very common misconception. I know my students stumble with this every once in a while, and that's the role of pesticides. Pesticides are not directly involved in eutrophication. They have their own environmental problem, but remember, eutrophication is about nutrient pollution. So it's going to be much more tied to fertilizer or wastewater, something that's going to input nutrients into the system. Pesticides are not going to do that. So I want to point out a practice AP FRQ. We're not going to do this one, but I just want to point out one part of this. This is from the 2015 exam about the Everglades. Great question. Not going to buy it for the Everglades from Florida. This is a great question. But I want us to zoom in on part B here. Part B says, in addition to water quantity problems, the Everglades is faced with a variety of water quality issues. For example, phosphorus concentrations in the Everglades have increased. So I says, describe how one specific human activity contributes to increase phosphorus. Explain one way in which an increase in phosphorus adversely affects it. And then I asks you to propose a solution for something we could do. So let's put this to real use. So I'm going to give you about 3 minutes to answer 2 parts of this question. So on a separate sheet of paper, again, let's answer this question. So I'll read the first part and then shut up for a few minutes and let you work. So students in an environmental science class at Fremont High School tested the water quality in a stream near the school. They were concerned about the possible pollution of the stream, which flows through a farm on which logs are raised. Shown below are a diagram that indicates the site where the student collected water sample, labeled A through D, upstream, downstream, and a table of the result of the water. So I'm going to be quiet and give you 3 minutes to answer just A and C. All right, I lied. I thought I was going to give you 3 minutes, but we're going to jump into it now. If you need more time, I apologize. So A says, did the hog farm cause it? That's what A is asking. Is the hog farm responsible for this water pollution? And so the answer is yes. And you get point for determining that, as well as using some of the data provided. We can see that the dissolved oxygen goes from a high level and dips down and starts to recover. That should be similar to that oxygen stack curve we just looked at. Then phosphates and nitrates follow a similar pattern. pH doesn't seem to change too much, but not really a factor. And then D says, describe the sequence of ecological changes. So immediately triggered you to the conversations we had about eutrophication from those models and video clips that we looked at. It's really interesting here. This is for 3 points and says 0 points would be awarded simply for saying that eutrophication occurred. That would be maybe an identify. It's not asking for an identify, saying describe a sequence of changes. So you would need to talk about the influx of nitrogen and phosphorus causing the algal bloom, the algae dying and being decomposed, the DO dropping, etc. So hopefully you feel a little confident answering this kind of an FR2. I think it's a really nice one to drive everything together. I do want to say, and this is a message from the College Board, that we know that not all students have access to the internet or device. We're working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity, or know someone who does, you can reach out directly to let us know in the URL below. I want to say thanks. Hopefully we'll see you again as we continue to look at Unit 8 and 9 and then review. So thank you very much, and I'll see you next time. Bye.
Hi, students. Welcome back to the third College Board virtual session where we're going to hit up a couple of more of the topics in Unit 8. Just remember that although Unit 8 is informally assessed on the exam, we want to make sure that you get a little bit of exposure to the content so that you feel that you've gotten the full depth and breadth of your AP Environmental Science course. There's again some pretty great topics you have to cover that you might see in your college AP Environmental Science studies or if you go on to take another AP Science exam. So my name is Amy Fassler. I teach in Northern Wisconsin at Marshfield High School. This is our first day of spring break today. We're kind of late, so we're going to start our warm-up with a little virtual spring break time, going back to the nice warm salt marshes and coastal ecosystems and mangrove forests that Dr. Sowell talked about yesterday. So let's get going and take a little bit of time to review that, and then we'll get into endocrine disruptors and some of the topics for today. So Dr. Sowell yesterday gave us some beautiful examples of the many valuable ecosystem services, and remember that concept is very global. I could be asked in an FRQ identify an ecosystem service of just about any ecosystem. So if I were asked to do that, to identify an ecosystem service, one of the most important examples Dr. Sowell gave yesterday that jumped out at me was their ability to absorb and filter runoff, and therefore improve aquatic water quality. The next part of a prompt might ask me to explain why that is an important service. And remember, when the skill or task verb asks me to explain why, I'm providing a reason for something. So sometimes those two prompts might even kind of be blended together. And I often like to instruct my students to put those transition terms in there. So this is an important function because it could prevent nitrates from entering the coastal ecosystem. And I want to keep going a little bit. I added just a little bit more. And again, if I have that transition word, therefore, I reduce the chance of algal blooms and hypoxic zones. You sometimes know that complete thought to make sure that you really explain why that's an important function. Because if I just stopped at they prevent nitrates from entering the coastal ecosystem, my question to you would be, well, what's my problem with nitrates in the coastal ecosystem? So that because and therefore are really nice prompts to keep you get that entire explanation of why that's important in this case. Sometimes on the AP exam when we're reading, a really common type of student response to this might be something like, well, the pollution goes into the water and that's really, really bad. That student understands that in the idea that process, that there's something happening within that ecosystem that's absorbing those nutrients, but you got to put a little bit of specific information with that. When you're asked to provide or explain why a particular pollutant that enters the ecosystem, what kind of impact it's going to have, you can't ever just say a pollutant. We need a little bit more specific there that demonstrates your knowledge of what you've learned in the course. And the same thing with explaining why. My explanation can't just say because this is very harmful. I need to make sure that my explanation is specific to, in this case, the pollutant I added, which was nitrates. All right, so we're kind of back into the idea of aquatic pollution. We're going to go ahead and take an overview, look at an overview of what we're going to do today. We're actually going to cover a little bit more than endocrine disruptors. We want to make sure we get through kind of the big ideas in the units 8 and 9 in the limited time we have. So I'm going to combine 3 different learning targets: persistent organic pollutants, endocrine disruptors, and bioaccumulation and biomagnification. And one of those topics really lends itself to the discussion of the next one. They flow very nicely together. Just like in the first couple lectures we've had, we related a lot of content back to Unit 5 on land and water use, because aquatic pollution a lot of times comes back to what am I doing? What is the impact of urbanization or clearcutting, large-scale logging, or habitat fragmentation, or mining, or industrial agriculture, or fish farming? So I want to be able to take those ideas and we're going to expand on that a little bit. There are a number of different skills that we'll focus on. A couple of those look familiar to you. Some of those you saw with Dr. Sowell. So let's go ahead and get started by looking at persistent organic pollutants. I'm going to introduce some new content here. It might be new for some of you. And there's a little bit of background information that we need, some vocabulary we have to kind of break down. So just sit back and kind of chill for a little bit while we walk through and start this story of these toxic chemicals and what happens when they enter the environment. So when I looked at my couple of essential knowledge statements here, this is really describing for me what a persistent organic pollutant is. This is talking about kind of relating that description and some of the chemical characteristics of that substance into its being fat soluble. And that property of those persistent organic pollutants is how we explain biomagnification. So let's break down a couple of the terms that we've got here. The first term is that this big class of compounds, this big class of toxins that can enter the environment are persistent. That means that they're not going to break down or degrade readily once they enter the ecosystem or once they enter the body of an organism within that ecosystem. It's kind of like your little brother or sister who's always poking at you, asking you for some help or come play with me. They're very persistent. They won't go away. So these are compounds that once they're there, they're going to stick around a long time. Next, these are compounds that are organic. That means that they contain carbon. Please have a molecule of glucose here. You guys looked at organic compounds in the unit on ecology when you did photosynthesis. So here's an organic compound. This is a molecule of glucose. Started out as inorganic CO2 in the atmosphere. Through photosynthesis, plants made this amazing molecule of glucose. These are each an atom of carbon. I've got 6 oxygens and I've got 12 hydrogens. So this is an organic compound, but it's not a persistent organic chemical. We have obviously a lot of natural organic compounds. Any kind of sugar, glucose, starch, any carbohydrate, cellulose, the material that plants use to make their stems and the structural components of their plant bodies, proteins, lipids, nucleic acids. So we're a carbon-based life form. There's lots of naturally occurring organic compounds. But when we talk about persistent organic compounds, we often talk about compounds that we're referring to compounds that are synthetic. So these are where I take carbon atoms, that's my raw material, to build a synthetic compound in a laboratory. All of those carbons come from petroleum refining in the petrochemical industry, and organic chemists take and tweak those molecules. So remember, I'm talking about things like everything from methane that we burn in our natural gas furnace to octane, 8 carbons long that I put mostly in the gasoline in my gas tank. And so chemists take those different fractions of crude oil and they manufacture synthetic organic compounds. Plastics are a synthetic organic compound. If you look at the labels of your clothing and you see any fiber like polyester or rayon, those are synthetic polymer compounds that ultimately came from crude oil. A lot of times when we talk about the synthetic organic compounds, they are present in their ring structure. It's a little hard to see here, but this is that straight chain glucose molecule that we had. And a lot of times we see that represented in sort of this ring structure like this, where, I mean, for glucose, there's an oxygen in my ring here, but otherwise all the members or parts of that ring are carbon atoms. And we'll look at those again in just a minute. What else describes a persistent organic pollutant? They're mostly non-polar fat-soluble substances. And this has a lot to do with that part of the essential knowledge statement was how do they get transported in the environment? Once they enter the environment, how do they get in my body or the body of an ecosystem? And what is the impact of that? So that's where we really look at the idea of biomagnification and bioaccumulation. And then they're particularly harmful because they have such a great ability to be transported in the environment and many different ways that we can get that exposure. So let's dig in a little bit deeper to these persistent organic compounds. And to do that, we got to review just a little bit of chemistry. So remember my description in my knowledge statement said that they're mostly non-polar fat-soluble molecules. Well, let's contrast that with water that's polar for a minute. If you remember the basic geometry of the water molecule, I'm going to get to the big idea here, so just bear with me. What we really care about when we say this water molecule is polar is that it has poles or ends to it, like the north and south pole of a magnet or the north and south pole of the earth. There are different ends to it. This is the oxygen. Remember we saw the little red oxygens in our glucose molecule. The oxygen end of the water is a little bit negative. It has a pole or a negative end, and the hydrogen ends are a little positive. Why do we care? Like, what does this have to do with these persistent organic chemicals? Well, if I have a chemical that I put in water, anything, we call water the universal solvent because it has those charged ends to it. Remember, opposite charges attract. So whenever I put something into water that has a charge to it as well, it's going to stick to that water molecule. It's going to go into solution. Non-polar substances, this is a big molecule of fat. This is like a triglyceride. This is the fat like I would eat if I ate a big cheeseburger and let a fat in it. So this is what that molecule looks like. And although we've got some kind of different stuff going on this end here, this is what I really want you to focus on. All of this molecule is non-polar. This is a bunch of carbon atoms with hydrogens all around it. All those electrons are evenly shared. There's nothing going on there where I have an end of this molecule that is positive or negative. We say it has no poles. It is non-polar. And this is a molecule of hexane. And just to show you, that's 6 carbons. It's kind of like glucose, except it doesn't have the oxygen, but it's 6 carbons in a straight line. And instead of these OH groups coming off of here, those would all just be hydrogens. And that is a product of petroleum as well. So let's see if we can visualize what I mean when I'm saying that something is soluble in fat, and then we'll make sense of why that's important. So let's see. Here's a little bit of water. You probably know that oil and water don't mix because they have different polarities. So when I put a little bit of oil into the water, that oil is going to form a layer on top of the water. Can you see that? There it is. See that oil is forming a little bit of a layer on top of the water. That oil did not go into solution in that water. Well, what if I put a little bit of oil in there with a little bit of hexane? This is hexane. This is that molecule that you see here that is also non-polar. And so when I put the oil and the hexane together in a test tube, they do not form a layer. Remember, my oil and my water form a distinct separate layer. They're not soluble in each other because there's nothing on this molecule to make it stick to the water molecules. But when I have two things that are non-polar, then one can go into solution. And so if you think about how this relates to toxicity, if I get exposed to a toxin in the environment through the food that I eat or my water supply, or I breathe it into the air and it's water soluble, it's going to dissolve. And I got a lot of water in my body. And even though that substance goes into solution in the water, like Kool-Aid goes into solution and I stir it up and I can't even see the Kool-Aid anymore. So that water soluble toxin gets dissolved and it's carried around through the water in my body, but it might impact my body as it's being processed by my body. And maybe the liver is detoxifying it a little bit, but ultimately I pee that out or I sweat that out or I excrete that because it's soluble in water and I excrete water every day through my digestive process. So it might have a little bit of an impact on me, but it's not going to be stored in my body. My body's going to flush it out when I pee. If I have a toxin that is fat soluble and it dissolves in that fat, I don't pee fat out every day. Think of all of the parts on your body where you got fat stored. So with that fat soluble toxin, like the hexane went into solution in the oil, that fat soluble toxin is now with my fat. It's being stored and my body is not going to excrete it or expel it. So let's just kind of review what we've covered so far. We have these chemicals that are synthetic organic chemicals. They're made with carbon atoms from petroleum in a chemical laboratory. They are persistent, they don't break down, and they're fat soluble so that my body is going to store them. It's going to accumulate in fatty tissue versus being expelled or peed out in my urine. So let's just take a quick check on that. This is a multiple choice question, but I really like it because notice this, there's still a command term here. It's still asking me to describe a way that persistent organic chemicals can be harmful. That's exactly how prompts might appear on an FRQ. So it's still good practice to look at those and pull out a good description. I'll let you have just a second to look at that. Oh, that should have been a pretty easy one. You probably would have known that 10 minutes ago before we started our discussion. So letter C, persistent organic pollutants are soluble in fat, so they accumulate in fatty tissue. Hold that thought because we're going to come back to it in a little bit. So let's look at a specific example of a persistent organic chemical now that we've kind of described them and hopefully have a pretty good feel for what they are and kind of something about their chemical nature that's going to help us be able to understand the impact that they have. And you've probably heard about DDT back in Unit 5 when you talked about pest control methods and you look at the idea of pesticide resistance and the pesticide treadmill. So here's the molecular structure of DDT. I'm not going to ask you to know that, but you know, even with our limited discussion, should say, aha, I see that there are carbons in a ring structure here. That's what this little kind of shorthand symbol represents. Each of these indicates a carbon in that ring. They're held together by double bonds. All we really care about is that I can see that this is an organic compound. Right away, if I'm talking about toxicity, my brain is going, there's a good chance that that's a persistent organic compound. So in our discussion of pesticides, you may have been introduced to Rachel Carson, and I'm going to play just a little bit of a clip because you're going to see how chemists first started making some of these organic compounds in the lab back after World War II.
Pesticides were always thought to be harmful. To the contrary, in 1947, Time magazine carried an advertisement claiming DDT was good for people, homes, and farms. It took 20 years before scientists realized how dangerous it was.
It begins with the war-borne development of DDT. This diabolical weapon of modern science saved billions of humans, but killed billions of insects. Man, with his newly discovered force, has at long last gained the upper hand in our age-old struggle. Just like these mosquito larvae, it came from laboratories where top scientists from famous universities and from industrial and government organizations collaborated to develop something new and different. They succeeded. They perfected Escort, the most effective weapon man has ever wielded against insects.
So one of the benefits of DDT is that it was really useful in controlling pests, and it reduced crop loss or increased crop yield, so that farmers could make profit and so that we could grow food to feed a rapidly growing human population in the United States baby boom, for example, after World War II. Rachel Carson first raised the alarm about the potential impacts of DDT in her book Silent Spring, and she sort of talked about that idea of the pesticide treadmill. Remember, our goal in using pesticides is not to kill every insect; it is to reduce the amount of crop that I lose. I expect a little crop loss, but not so much that I still can't make a profit. So Rachel Carson believed that there may have been a role for pesticides in controlling insect pests that reduce crop yield. But like any good scientist, she started asking questions, just like we want you to ask questions, both as young scientists and consumers that may be exposed to these persistent organic chemicals. Is there a certain dose or concentration that's safe? What happens to that DDT after I spray it out of the airplane and it lands on an aquatic ecosystem? So Rachel had a lot of questions, many of which were answered or addressed as a result of the publication of her book. So let's take a second and see if you can identify something about DDT as a persistent organic chemical. Again, this is looking at the task verb describe. So if on an FRQ, you were asked to describe something, you are listing characteristics of it. Take a second and look at that one. And the correct answer is A. Notice that statement B is a correct answer, and they alluded to that a little bit in that film clip that we just watched. They talked about the benefits of it, and there are benefits both from reducing crop loss to killing vector insects that transmit really harmful diseases that could kill large numbers of people. Things like malaria, typhus, Zika virus, and we'll be looking at those vector diseases a little bit more next week. Obviously, the correct answer is that it's very stable, and so DDT is going to stay in the soil or whatever ecosystem it ends up in for a long period of time. Okay, so hopefully you've got some pretty good general idea of what those persistent organic chemicals are. Stay around a long time, have carbon, and they're fat soluble because they're non-polar. They've got those carbon in rings usually because that ring structure is more stable than the straight chain. Okay, so now we can get into endocrine disruptors. This is one of my favorite topics. Endocrine disruptors, and we often call them estrogen-like chemicals. I'll show you that term in a minute. They are a type of persistent organic pollute. So I already know a lot about it just by knowing it's a persistent organic pollute. I know it's going to stick around a long time. I know that it's a synthetic compound that's manufactured in a lab, and there's a likelihood that it's fat soluble because most of those organic compounds are kind of fat soluble. So let's look at our knowledge statement. The first knowledge statement describes an endocrine disruptor. They interfere with normal endocrine system. Okay, we'll explain that in a minute. And then this is the impact that they have, and we'll look at that as well. And we'll look at again a couple of those skills or practices. So here is kind of a simple diagram that explains how endocrine disruptors work. First of all, the endocrine system is our system of glands that produce hormones. And when I look at what they regulate, I could really have made that list even 10 times longer. We have so many different hormones that do so many different things. They regulate metabolism. That's like the way my body processes and absorbs different nutrients. Growth, development, sexual reproduction, development in the embryonic stage is influenced. We now know that endocrine disruptors can influence everything from aggressive behavior or learning disability. So the list of things that are controlled by our endocrine system, the number of hormones that control different processes is just really a big list of things. So endocrine disruptors have the potential to disrupt a lot of different activities. What you kind of want to think about when we think about hormones, like insulin is a hormone you've probably heard of. And what insulin does is there's a signal that released if things are working right in my body, that if I just eat a diet that's got, or if I just ate a lunch that was really high in simple sugars and the amount of glucose floating around in my blood is really high, insulin says, oh, wait a minute, I'm going to go gather up some of that glucose and I'm going to pack it away in a compressed glycogen form and I'm going to store that away in case this person doesn't get any food for a while, and then I can release it and they'll have glucose for energy. So you can think of these hormones as like little switches that turn a process on or turn a process off when everything's functioning the way it should. So here, for example, is my cell. And when a normal molecule comes along, like an estrogen like chemical, and I'll show you the real molecule of that in a minute, there's a certain end. You may have looked at, have been seeing images of the coronavirus, and they talk about those glycoproteins, those protein spikes that are coming out of it. Well, it's pretty much the same idea of what happens when a hormone has to bind on the surface of my cell. Here's my normal estrogen hormone. Here's my cell. There's a perfect fit there. And the minute that estrogen binds in that cell receptor site on the surface of the cell, it's kind of like it opens a door. It turns a key, and a whole process of other chemical downstream reactions can start to happen. And you may recognize the hormone estrogen. It's the hormone that stimulates the development of secondary female sex characteristics, and it's important for determining cycles of ovulation and release of eggs and implantation of eggs. It's a very powerful hormone that controls a lot of reproductive functions in my body. So let's say, for example, and I'm going to show you these images now, you may have heard of the chemical BPA. The chemical name for it is bisphenol A. That's why we call it BPA. And you may have a water bottle that literally is labeled, oh, just so you know, this is BPA free. So BPA is a persistent organic chemical. It is one example of an endocrine disruptor. Persistent organic chemicals, endocrine disruptors are one sort of big group of organic chemicals. There are other things like DDT as well. So here is that molecule of estrogen that just bound on the surface of my cell. Here's the molecular structure of it. Here's its little skeletal structure. We recognize now that this is a ring of carbon atoms. So simply knowing that, I know a lot about this. I know it's probably persistent. I know it's probably fat soluble. I know it's something that doesn't occur naturally anywhere on, estrogen is a naturally occurring hormone that works in developing secondary female sex characteristics. Here's the molecular structure of BPA. And again, now I already know a lot about that. I know that it's carbon. I know it's organic. I know that if it's a persistent organic compound, this doesn't occur if it's a synthetic compound and it is man-made. This doesn't occur anywhere naturally on our planet. And that inherently should kind of be raising some red flags to you, because you know how fine-tuned ecosystems are and how they've evolved to work well with what they're given. So this is the synthetic compound. And when I look at it, I'm going to give you just a second to look at the structure of BPA, the synthetic compound that I use in plastic. It's added to change the properties of that plastic, make it, I think, more durable. And here's the structure of that natural hormone, very powerful hormone in reproduction, estrogen. So when I look at them, it appears as if they've got some little OH groups, hydroxyl groups coming off them here in kind of the same place. So if I look back at that original model we were looking at, here's the way estrogen-like chemicals work. Here's my estrogen that bound in there really tightly. Maybe it was this OH group that bound in that cell surface and it made a really tight fit, and that there was a chemical reaction that occurred when that hormone binds on that cell surface. Now, here's my BPA, and it's got some pieces off of it that look kind of like estrogen. So for all estrogen-like chemicals, kind of two things can happen. Either this BPA molecule can kind of try to fit on that cell surface, and it doesn't quite fit good enough, but it's blocking it so that the real estrogen can't get in there. Or perhaps it's got enough similarity in chemical structure to an actual hormone that it can actually bind in there, and my cell thinks that estrogen is binding, and my cell is turning on all the processes that would be turned on just like if estrogen had bound there. Very powerful secondary development of secondary female sex characteristics. So let's see if we can bring this full cycle to the impact then on ecosystems. So here's a graph. I want to make sure we got a little graphic interpretation in. One of the biggest impacts of DDT, for example, on ecosystems was the thinning of eggshells. Remember that DDT molecule looks a lot like an estrogen molecule, and DDT had a big impact on, in this case, an osprey. Oftentimes, birds that are at the top of the food chain, tertiary consumers, fish-eating or meat-eating birds, for example. And if you think about it, the process of producing that eggshell to care for the fertilized egg, all is going to be all of the processes that are involved there are stimulated or initiated through estrogen binding on a cell surface. I'm making this sound pretty easy, but you're getting the big idea. So what happened when we used a lot of DDT, and that DDT ended up in an aquatic ecosystem, and a fish ate that, and then the osprey ate the fish, we saw that there was a great reduction in large bird of prey populations because of eggshell thinning. And this graph shows DDE. DDE is what we call a metabolite of DDT. Remember that even if that substance is somewhat water soluble, it's going to still have impact on my body as it's going through it. DDE is the sort of the breakdown product of DDT. So if I'm going to do an experiment to assess the concentration of DDT exposure, it's very easy for me to actually measure the concentration of what's excreted, if you will, or the product that broke down. It's sort of an indirect way of assessing DDT exposure. And the point that I really want to make here is this negative relationship, because this is a sort of a misconception that a lot of students have about a positive and negative relationship when they look at information represented graphically. So this is my independent variable. The amount of, we're just going to say DDT, the amount of DDT determined the thickness of the eggshell. And I can see that as I increase the concentration of toxin, I decrease the thickness of the eggshell. I got a nice trend line on there showing me that there is a negative relationship. There's still a relationship, but increasing the toxin doesn't increase the thickness. Increasing the toxin decreases the thickness. And as you can imagine, if the eggshells were very thin, the developing chicks just never reached it to maturity and really harmed a lot of populations of large birds of prey. One of the other really interesting, unfortunately interesting but kind of scary thing that we're also seeing with endocrine disruptors is feminization in amphibian or fish populations. Any or aquatic organism, and we're going to come back to why aquatic organisms in a minute, but amphibians are really good indicator species because they live part of their life cycle on land and part in the water. They are very sensitive to pollutants in their environment and changes in the concentration of those. So what happens when these strong estrogen-like chemicals enter the aquatic ecosystem is that those amphibians or fish are getting very large doses and they are losing their masculinity. We've actually seen examples of there's almost no males left in the species anymore. And this is kind of what Rachel Carson started doing with good science work and what we as good scientists want to do. We don't know all of the impacts of these endocrine disruptors, but we certainly have good questions we want to ask. If a vertebrate animal, if an amphibian is being impacted at a certain concentration of these endocrine disruptors, can they function the same way in a human? That's certainly a good question to ask. Much of that exposure comes from pharmaceuticals, and Dr. Sowell is going to talk about waste treatment tomorrow. But even if I don't throw my pharmaceuticals, like my leftover pills, I could throw them into the river or I could flush them down the toilet. There's still another way that they could enter the ecosystem. Anybody think about that? Even if we're not directly or indirectly dumping leftover pills, they could be coming out through my urine, or the metabolites, the breakdown products of those things could be coming out in my urine. So this is a difficult problem to address, and one of the things that you look at in sewage treatment. Let's just take a quick how do you know what you know here and look at a question on endocrine disruptors. Which of the following best describes the action of an endocrine disruptor? And you should have been able to pick out letter B. They block the receptor protein binding site. That part we didn't go into a lot, maybe a little bit, so that the hormone can't receive a signal. So remember, that can either bind in there and act just like estrogen and turn that on, or I can block it and prevent in this case, estrogen, but it could be other hormones as well. These are far-reaching compounds. I just focus on the estrogen. So let's wrap up our new material by looking at bioaccumulation and biomagnification and bringing these concepts all together. Notice here, we've already talked about DDT. PCBs are kind of like BPA. They're another persistent organic compound. So the last thing we want to look at is mercury. And you've got the essential knowledge statements, which are basically a description or a definition of bioaccumulation, which is the buildup of a toxin in an individual person. I'm taking in a toxin at a rate greater than I can pee it out or expel it or excrete it. So it's accumulating in my body. Biomagnification implies that as that fat-soluble toxin, if another organism eats that or down-level trophic level organism in the food chain, because that toxin is fat-soluble, each organism above it, its concentration is magnified. It's kind of a hard thing to visualize. So I'm going to show you that in just a second. Let me just quick first show you where that mercury comes from in the environment. Burning coal, you look at that in your energy and your air pollution unit, releases the mercury. The mercury often falls with precipitation or as dry deposition, falls on a lake, an aquatic ecosystem, and down in the sediment of that lake, there are microbes, there are bacteria that are converting that to a methyl mercury. Oh my God, they're putting that mercury on the end of a little organic molecule. Now it's fat soluble. So now when this little fish is eating some algae in there, it's getting that mercury now is an organic compound that's fat soluble, and it can accumulate in that fish. That big fish is eaten by the little fish is eaten by a big fish, which is eaten by a human. And what happens in the process of biomagnification is that concentration increases as I go up the food chain. And this should look super familiar to you. Remember the 10% ecological efficiency rule, that these zooplankton only get 10% of the energy from the trophic level below them? Well, let's take that idea and relate it to the idea of biomagnification. So here are some little zooplankton, phytoplankton, fish, eels that eat the fish, and there's that osprey at the top of the food chain. I'm going to let you watch this quick little simulation where each M&M is going to represent 1 part per million of methyl mercury. So the whole way this works is that each of those little zooplankton eat 5 phytoplankton, each of the fish are eating 5 of the zooplankton, which each of the eel are eating 2 or 3 of the fish, and the osprey ends up eating both eel. Notice how pretty quickly the osprey got all of that persistent organic chemical. It got all of that mercury that worked its way all the way up through the food chain. It biomagnified. So as we're wrapping up, here are just a couple sources of some of these toxins. I did want to point out breast milk because that's something people maybe don't think about. But if I'm a meat-eating nursing mother, I could be, if I'm eating fish that have a high concentration of mercury, my breast milk that I'm feeding my child may have a very high concentration of mercury. And breast milk is actually a really great human fluid, if you will, to use for studying toxicity because I can get samples of it pretty non-invasively. And the nice thing about it is I can get toxicity exposure for both the mother and the child that's consuming that breast milk. So let's wrap up with just a little bit of guided practice. Identify one human activity that releases mercury and describe how that mercury is transported. And finally, explain why there are greater health risks associated with eating large predatory fish. These are both pretty much pre-response questions that we've seen before. Burning coal releases mercury into the environment. A mistake that students often make is they don't burn a fossil fuel. So don't just say using coal, because if I have a hunk of coal sitting here, it's not releasing any mercury. Mercury is transported. Remember, I'm describing a process, how that happens, and falls onto water or soil, and then the mercury can biomagnify or increase in concentration through the food chain. I think we're about out of time, and so I'm going to leave this practice math problem up here. You can go back and check it. The one thing I wanted to point out when you look at your dimensional analysis work here, please make sure that whenever you're setting up your dimensional analysis, that you have a unit that gets canceled. That's one of the biggest mistakes students make, and I think we hit a lot of those targets. Sorry, we went through that mathematical calculation pretty quickly, but I wanted to make sure, and Tony, thanks for coming. If you take an advanced environmental science class in college, or just being a good consumer, be a good scientist, ask good questions, and tune in tomorrow when Dr. Sowell is going to take you back to wastewater treatment plants and look at how we solve some of these problems with toxicity. Thanks, guys.
Hello, everybody. Welcome back to our virtual lessons for AP Environmental Science. My name is Dr. Sowell, and I teach APES at Darnell-Cookman Middle High School here in Jacksonville, Florida. So, just to get our brains warmed up, we're going to revisit what Ms. Bassler ended with last time. She was in the middle of a, not in the middle, but she was finishing up a conversation about bioaccumulation and biomagnification and talking about mercury. So, we know that that's part of electronic waste or e-waste, any kind of discarded electronic devices, television, computers, cell phones, things like that. So, we're going to pick up with the FRQ that she introduced right here at the end of it. So, it says 30 million mobile devices were sold in 98. The number sold increased to 180 million devices in 2007. Discarded mobile devices being part of the electronic waste stream E-stream. Mercury is often present in e-waste. So, there's three parts to this question. First one is just an identify a negative human health effect, and then to calculation. Let's go over the answers to those really quickly. So, the first one was identifying negative health effects other than death associated with exposure to mercury. So we see all those neurological problems, kidney damage, vision impairment, paralysis, pneumonia disease. I will say the pneumonia disease is a really fascinating case study of bioaccumulation, biomagnification, and mercury. So I would highly suggest Googling that. Going on YouTube and see about pneumonia is really fascinating. So that was for one point, just to identify. The second one is a calculation. So remember that you have to determine which type of method you're going to use, and then you have to apply some mathematical work, and then get an answer with appropriate unit. So this question says each mobile device contained 0.03 grams of gold. Calculate the number of grams of gold that were used in production of mobile devices sold in 2000. So we knew there was 180 devices. Each device had about 0.03 grams of gold, and that resulted in the devices canceling out the way we set up our dimensional analysis. Always remember, when you're doing calculations, have a unit every single place you can, and the dimensional analysis setup will help you cancel out unit, and that leaves you with 5,400,000 grams. The second part of this said, assume that the average mass of each device was 0.1 kilogram. The EPA estimates that about 10% of the mobile devices sold were recycled. So now we want to know what is the mass of the mobile devices that were not recycled. So that would mean the other 9%. So we have 180 million devices. Each device has a mass of 0.1 kilogram, and we are interested in 90% of that because we know 10% was so again our device unit canceled, and we're up to 16,200,000 kilograms. All right, now we've got our brain warmed up in our AT way. Let's jump into today. So here's our goals for today. Number 1, solid waste disposal. Number 2, waste reduction method, and number 3, sewage treat. So this is coming from topic 8, 9, and 10. And again, we're going to revisit practice number 2, visual representations, and how we can use those images in environment. So overall, my goal of today is for you to leave the next, or once we're done here, we will talk about where does the toilet go and where does the trash go. So we have processes that are interesting to talk about. So again, what happens after the flush and what happens after the throwaway. So before we get started into this topic, though, I would suggest reviewing a few things just so that you're comfortable with the conversations we're having today. This will be a really great review of the hydrologic cycle because there's some issues with groundwater that we're going to discuss today. Also fossil fuel. We're going to talk about in particular methane, which we know is a main component of natural gas. So be sure you remember how natural gas is turned into this. And finally, soil composition and properties. Some of the physical characteristics of different soil textures are going to come into play here. So that would be another great thing to loop back in and review. So let's jump right into it. The first thing is solid waste disposal. So here we've got a picture of a dumpster. It's like they're cleaning out some house or garage. We see lots of plastic bags, paper bags, and wood. Who knows what else is there? If we are going to quote unquote get rid of this, where does it go? And that's our question today. What happened to it? So by the end of this section, you'll be able to describe solid waste disposal method. To get there, we are going to define what solid waste is. Basic definition. We'll learn about a sanitary municipal landfill where most of our garbage goes, and then also solid waste incineration, which in some places what they do with the solid waste. And finally, we'll look at some illegal ocean dumping and some of the very specific environmental consequences that results. So, what's solid waste? It's not a liquid or a gas. It's solid waste, and it can come from a lot of different places, from industry, from agriculture, from home. For the scope of what we can cover today, I'm really going to focus only on municipal solid waste because that's what I generated this morning. That's what you generated today. That municipal or city waste, or everyday garbage trash. So, where does that stuff go? It goes to a landfill. And I'll be honest with you, before I started teaching this class, I don't think I really had a strong understanding of the anatomy of the landfill and how the structure of the landfill design actually helps to mitigate some of the environmental effects of the landfill. So hopefully by the end of today, you'll understand why we build landfills the way we do, and then some of the environmental consequences that exist. So in order to define what a landfill is, I think it's really useful to contrast that with something like an open dump. It's a place where people might be growing trash. But this is not a landfill. This is not regulated. There is no oversight to this. It's trash on the side of the road or in a field somewhere. And there's some very specific problems associated with that we can then try to solve with a landfill. So the first one is smell. Obviously, it's decomposing material, visually unappealing. No, this is not exactly someone's ideal vacation destination. And also trash. If there's a big wind, some of the stuff is going to blow all over the place and become litter. If this starts to catch on fire, this could be a real environmental and human health hazard that we should avoid. Vermin. Love that word. Vermin. Kind of a little pest that might be around, a rat or mosquito, or in this case something like pig, animals that might be coming in, and some of those animals might be carrying disease. The last two is methane and groundwater contamination. So methane getting into the atmosphere and something from this dump actually contaminating our groundwater. So I'm going to focus quite a bit here at the beginning on those two particular environmental problems associated with the dump. So let's look at this dump. So this is not a landfill. This would be just an orange dome which kind of represent this open dump where we dump all the trash. And I want you to imagine the dark brown dot as pollutant. All it takes is a good rain, and rain is going to percolate down through the landfill. And as it goes, it's going to grab onto and pull out those toxins and pollutants. Those toxins or pollutants are going to leach out. And so therefore the resulting liquid is called leachate. Well, from your understanding of the hydrologic cycle, remember that groundwater can be contaminated from surface water. So this water that has percolated all the way through the landfill is now going to continue to travel and recharge maybe your drinking aquifer or another body of groundwater. But now that leachate contaminated that water. So this is clearly a problem of an unregulated open dump. Another problem is methane. So here's our dump again, here's our trash, and eventually the microorganisms that are decomposing the trash are going to run out of oxygen. It's going to be switched and compressed way down, but it's not going to be finished decomposing. And so what's going to start happening is anaerobic decomposition. When there's absence of oxygen, one of the main byproducts of anaerobic decomposition is methane. So methane is going to be generated in this landfill, get into the atmosphere where we know it is going to be one of the major greenhouse gases. So this is going to be implicated climate change. So definitely recognize that landfills are a significant contributor of methane. So we're talking about an open dump here, but even a landfill has a problem. So based on that list of problems, we designed a sanitary landfill where we put most of our solid waste here in the United States. However, we still have the issue of groundwater contamination and harmful methane release. So what do we do to work with some of those problems. Let's just look at this diagram. The first thing I want to highlight is that portable fences used to catch windblown debris. Windblown debris. There we go. There's one way to eliminate that windblown trash or litter. And then we see that every day after the trash is unloaded and pushed into little piles, it's compacted and covered daily with oil to keep out vermin and reduce odor. So it's almost like a cake, like a layer of trash, layer of soil, layer of trash, layer of soil. And that layer of soil keeps out the vermin and regulates the odor a little bit. And then we also get these large pipes. And it says pipes sunk through compacted layers collect the methane gas to either burn it off or convert it into energy. So we just talked about how methane is a problem in a dump. So in a landfill, a lot of that methane is captured and used later. And down here it says part of the drain grid. Perforated drains collect leachate for treatment. So at the very bottom of the landfill, we're going to have these perforated pipes in which that leachate is infiltrated and percolated all the way down into the pipe and collected. Finally, at the bottom it says layers of compacted clay and high-density plastic liners protect groundwater. Why clay though? So if you remember back to the physical properties of soil, we remember that clay has very low permeability. So it's going to act as a really nice boundary between the leachate and the groundwater. So a layer of plastic and clay is a great lining to the bottom of the landfill. Well, let's just take a look at those issues of odor, visually unappealing, trash and litter, fire, vermin, groundwater contamination, and methane. We solved a lot of these, and some we've made a lot less of an impact. However, 16% of all the methane emissions in the United States still come from landfills. So landfills are still a very significant source of methane, which again is a greenhouse gas. You may notice that the one category above that is called enteric fermentation. It's an odd phrase if it's not familiar to you. And again, that's just if you remember from our discussion of livestock and meat production, that methane is a byproduct of the digestive system of these ruminants. So now we come to a unique thing, tires. So it's not something you think about, but tires can't be recycled too well into new tires once they're old and not used anymore. So they get thrown away a lot. And unfortunately, they sometimes gather top of landfills. And if they catch on fire, an incredibly bad source of air pollution. So a lot of times landfills will not take tires, or if they do take them, they'll require them to be shredded really finely before use. But that's not the only bad part of tires laying around either in a dump or a landfill. It has to do with mosquitoes. If you think about it, that space in between the two sides of the tire can collect rainwater, and that stagnant rainwater becomes a really great breeding ground for mosquitoes. You see those mosquito larvae in the top left doing their cute little up and down dancing oxygen. But a single tire could breed several mosquitoes, and then thousands of tires in one place you can see would have a very negative impact, especially in terms of diseases like malaria or Zika. So if you think about all of that methane, you should be starting to connect that to natural gas and think, well, maybe we could use that. Absolutely we can. Some places will actually collect the methane and use it to generate electricity. So just as a reminder from our unit on electricity, when we're taking fossil fuel, coal, oil, or natural gas, and turning that into electricity, we typically follow a series of steps that you should be able to drive. So first of all, we have to collect and transport this methane. We've got the pipe and systems by which we can do that, collect it and transport it. Then we're going to burn it. The heat from that is going to boil water to steam or hot air. And that steam is going to spin the turbine, and that's going to rotate a generator to generate electricity. And be sure that you can not only describe the process by which the electricity is generated, but also understand the source of the methane from that anaerobic decomposition within it. So we're going to show a couple minute clip here, just as a nice overview of what we talked about.
Finding a suitable site for a landfill can be complex. Landfill operators will work with regulators to ensure the new facility is located in the right place. Some places, like properties near wetlands, will be carefully evaluated for any environmental concerns. Impacts on nearby traffic will be analyzed. The site will also be evaluated to understand the land, groundwater, and surface water in the vicinity. Community feedback is important to consider, and meeting environmental and land use standards are a must. Once the site is approved by the regulator, the first step is to follow permit plans for sound construction. The second step is to secure the base of the landfill to provide a stable base for the liner. A two-phase composite liner is installed on the base and sides of the landfill. Leachate, a natural occurrence when waste is in contact with water, is collected through a system of drains, pumps, pipes, and hoses that move leachate away from the landfill. The leachate collection system will act as an effective biological filter by removing excess moisture from the bottom of the landfill. A groundwater monitoring system is installed to ensure the landfill does not impact groundwater at the site. The monitoring system acts as an alert in case additional measures may be needed to protect neighboring properties. Groundwater quality is protected at all times. Access to the site is carefully controlled for safety, and waste is screened by appropriateness as required. The landfill is ready to receive waste that has not been recycled. Equipment compacts the waste each day before daily cover, soil or tarps, is placed to avoid potential littering and odor. Gas wells are installed to capture methane generated by the waste. Once full, the landfill is covered with a cover system approved by the regulator. Groundwater continues to be monitored, and methane gas is collected and destroyed or turned into energy or fuel. When the landfill stops accepting waste, regulators will approve its closure and will monitor its safety for 30 years or as required by the regulators. Then, controls will be put in place to keep the property secure for the future. The property surrounding the closed landfill can be used for commercial or industrial use, but commonly, the property is used for green space, suitable for recreation or habitat conservation. We strongly support wildlife habitat conservation at our landfills through our partnership with the Wildlife Habitat Council.
So the volume of stuff, of solid waste in a landfill is an issue. The more solid waste in the landfill, the more methane that's going to be generated, the more leachate that's going to be generated, and those two things we have to deal with. So anything that we can do to reduce the volume of solid waste in the landfill is something we should explore. And one of those ways, which is pretty common, is incineration. So many places around the world will burn the solid waste instead of sending it to a landfill. The majority of our solid waste here in the United States still goes to a landfill, but incineration is not uncommon. Clearly, the first thing that should pop into your mind as soon as we hear about burning something or combusting something is air pollution. So while the pro is it reduces the volume, we now have to deal with the subsequent air pollution that comes up with that. So this last part of where our solid waste goes, we're really going to look at something a little bit more nefarious and illegal. So some countries dispose of their waste by dumping it in the ocean. Now, certain countries have laws against that, some don't, but this practice has led to a lot of plastic in the ocean. You can see this is a picture of a beach somewhere with lots of plastic pollution all on the beach. Well, while it might be unsightly and an environmental problem here on shore, it has a very specific and dangerous consequence to wildlife. So we're going to take a look at a clip from the United Nations that really talks about this concept of plastic pollution in the ocean. I will warn you, towards the end of the video, there is a dissection of a seabird, and we're looking at some of the plastic that is eaten. So if that kind of image makes you a little squeamish, feel free to turn away for this moment of the video.
Garbage thrown away in the United States can make its way to Antarctica. Plastic in our coastal waters is pulled into the center of massive wind-driven, churning circular gyres. There are many other ocean currents also diverting the trash all around the surface of the ocean. In reality, there's just one ocean with no boundaries. Lord Howe Island is the World Heritage Site and home to migratory seabirds like the shearwaters. Seabirds are incredibly helpful because they act like an army of scientists. They travel thousands of miles across the ocean. They pick up plastic off the surface of the ocean. They bring it back to their rookeries where they feed it to their chicks. And that provides an incredible amount of scientific data in terms of where the plastic comes from, its distribution, and how it breaks up on the ocean surface. Dr. Jennifer Lavers, she's devoted her life to studying the plight of seabirds. Shearwaters are incredible birds. They migrate thousands of miles, stopping only here to breed.
Yeah, the stomach's very, very full, and if we look here, there's some very dark pieces, some very light white pieces, and if you see, as I push on this, it's absolutely rigid, completely full of plastic all the way up.
Oh, look at that.
Absolutely no doubt that this bird died as a result of that plastic. That is literally a gut full of plastic. It's quite alarming, isn't it?
Oh, it's awful.
Range of plastic types and colours, got everything from the blues and the reds.
His stomach's just filled with it, big pieces too.
Big sharp pieces.
Oh, wow, look at the size of that big wet piece.
That is an enormous piece of plastic.
Unbelievable. Look at the size of that. Jen, I counted 234 pieces of plastic out of that one bird.
So you can see a lot of really dramatic footage there of this plastic becoming part of this bird diet. So we really got to think about our single-use plastics and what are they doing to the environment. A lot of the single-use plastics, like plastic bags, we might use in a grocery store. While that has a purpose perhaps in our daily life, it may have some negative consequences beyond our use of it. So we're really going to look at two ways that we could maybe reduce the amount of solid waste going to the landfill. We are only going to talk about these briefly because I want to spend some time looking at sewage treatment. So two of the most common ways are recycling and composting. Now, you've been hearing about recycling probably your entire life. Composting may be a little bit new, but both of these can help reduce the volume in the landfill. Recycling is a great way for us to kind of reduce the demand on our natural resources and some of our minerals. However, it is pretty energy intensive and costly. So not only are we talking about having to simply store and transport these materials to a recycling facility, the facility itself is going to take some energy and money to turn those methods or turn those substances into something new, recycling it into a new product. Composting is a little bit different. So you're taking just the organic matter and you're using decomposition to turn that into fertilizer. So it can happen on industrial scales. You can have large industrial facilities taking lots of organic solid waste from a city and composting it, or it can happen in your backyard. You can take some of your organic waste from your kitchen scrap, let's say, or yard waste, and compost it in a pot. Now we do have the downside. They're a little similar to what we saw in the dump of the odor of the rodent, but there are ways to lessen the thing. I know I particularly use at home as well as in my classroom vermicomposting, which is using earthworm, red wheeler earthworm, to help decompose. Every 6 months or so, I get these really great bags of worm acting for great fertilizer. So recycling and composting are two unique ways to reduce the volume of solid waste going into the land. So let's just do a quick check for understanding. I'll give you about 30 seconds to answer this question, please. So hopefully you saw that the incineration could lead to some air pollution. I now want to point out the 2016 FRQ about municipal solid waste. So it starts with a graph showing us the total municipal solid waste as well as per capita municipal solid waste from 1960 to 2012. There is a part A to this, which is more calculations, but I want us to focus on B through E. So B says identify a disadvantage of waste incineration, and I identify a disadvantage of waste disposal in landfill. So you should be able to identify a negative consequence of both of those. Then we go into incineration, and this is the one I would like you to actually practice now. So C says describe the steps of a process used to produce electricity from waste buried in a landfill. So again, note the password describe, which means provide the relevant characteristic of a specific topic here, electricity generation from the waste buried in a landfill. So take 30 seconds and jot down on a piece of paper what you answer for C. All right, so let's take a look at these answers here. So this is worth 3 points. It says 1 point for each step in the process of generating electricity from landfill gas. So there's 3 parts of this. So step number 1, get the methane, get the fuel. Step number 2, combust it, producing that steam or hot air. And then finally, using that to generate electricity going from mechanical to electrical energy. The steam spins and rotate the turbine and the generator. So our second big topic we're going to look at today is sewage treatment, wastewater treatment. So by the end of this little section, you should be able to really describe the best practices in sewage treatment. So to get there, we're going to go to a sewage treatment plant, a wastewater treatment facility, and we're going to look at the stages of wastewater treatment. So first is primary, second is secondary, third is tertiary, and then fourth step is disinfection. So we'll walk through each of these phases and give some examples. So again, what happens after we flush? Most people really don't think about this too much, but for the vast majority of homes, this is going to go to a wastewater treatment plant or sewage treatment. And again, just like the landfill, it has specific design features to make it operate properly and to minimize environmental impact. So let's take a look at those. So the first one is primary treatment, and this is physical. So you'll notice I underlined the word physical just to remind you that primary is physical. It's going to start with using a screen or a grate to filter out solid material. So this is going to be things like plastic, paper, somebody's toy, the car that they drop down the toilet, whatever it might be that's solid. These grates are going to really help you grab it before it goes into the wastewater treatment plant. And then we're going to let the water settle. So we're going to take fast flowing water, slow it down, and let it go move a little slower through the plant. And all of these particles that are in the wastewater, a lot of them can settle out. So again, we're not using any chemical or biological treatment here. This is all physical, filtering and settling. And then we go into secondary treatment, and this is when it becomes a zoo. So we've got all of this anaerobic bacteria that is going to now break down that organic material and turn it into sludge, which settles down to the bottom of the tank and be taken elsewhere. But this is aerobic decomposition. Now, why do we have all these bubbles in here? That's really important to talk about because if you remember from our conversation the other day on eutrophication, the point source pollutant coming into the stream is going to demand a lot of oxygen because these microorganisms, these decomposers, really want a lot of oxygen. So what we see in the stream is the oxygen sag down, the oxygen sag curve, because the oxygen is being used up. So in order to make a wastewater treatment plant function perfectly, you're going to inject lots of air into the water. And the tertiary treatment is not one we're going to go into too much detail, but just know it is an advanced step to remove any additional pollutant and to grab out as much nitrogen as possible. And then finally, before the water is discharged to wherever it's going to go, into a river or wherever it might go in your area, it needs to be disinfected. So we want to get rid of the bacteria that might be in that water. Common thing to use is chlorine. There's some environmental consequences of chlorine. So some places are using ozone or UV light. These are just large UV bulbs. And once they're lowered into the water stream, the wastewater flows through it and the bacteria get killed. So we're going to take a look at a clip from National Geographic. This is a quick tour of a wastewater treatment plant in England.
Waste from London's toilets, sinks and gutters is carried away by a network of interconnecting Everlogic pipes designed and built by sewage superstar and pioneer Joseph Bazalgette. It all ends up here as sewage treatment works.
This is Beckton Sewage Treatment Works in the east of London, and it's Europe's biggest. It was originally part of Joseph Bazalgette's scheme, but I'll tell you what, sewage treatment has really moved on since his day.
In the 19th century, sewage was simply stored here in tanks, then pumped out to the river at high tide. So you'll be pleased to know today's process is a lot more refined, and takes just 4 hours for raw sewage to be clean enough to return to the river.
Every day, this treatment works handles the sewage from 3.4 million Londoners. That's an astonishing volume. It equates to 34 Olympic swimming pools every hour.
So how does it treat the byproducts of our late beer sessions and trips to the local curry house?
The first process happens here at the inlet works. Using these screens, large lumps like bricks, wood, rags are raked out.
Once collected, these large objects will all be washed and sent to a landfill site nearby.
They've even had half a car here.
Meanwhile, the remaining sewage passes on to the next part of the process into these primary settlement tanks.
Now, very basically, it enters at that end and flows relatively slowly this way.
Over the top of each tank is a moving bridge, which has two blades to remove solid organic material from the sewage. The top blade skims the scum from the surface, while a second submerged blade dredges the heavier settled sludge from the bottom of the tank. All this solid sludge is then sent for further processing.
The remaining sewage then flows down this way towards the secondary biological treatment process.
And here it is. In these tanks, the sewage is mixed in with billions upon billions of bacteria, so all the dissolved materials that still remain can be biodegraded.
And pumping.
So let's debrief now of what we just talked about. So our goals overall were to understand solid waste, where does our trash go? What are some methods that we could reduce the volume of solid waste going to that landfill? And then finally, sewage treatment, primary, secondary, tertiary, and disinfectant stages in wastewater treatment. So let's look at some actual questions that you might be asked about wastewater treatment and solid waste. So just a reminder, really know those task verbs and try to figure out what each one is asking and how that kind of direct what you're going to write. So this one comes from the 2012 exam. This is FRQ number 4. It's a great review of our conversation from 2 videos ago about the wetland. So it asks you to describe a wetland, to complete a little food web here in the middle, some economic benefits of a wetland, specific activities that might degrade the wetland. I want to focus on E down here, E at the very bottom. It says wastewater treatment plants perform some of the same water quality improvement functions that natural wetlands perform. Explain how wetlands perform. They're the equivalent of primary and secondary treatment. So keep in mind that the word explain is asking for a little bit more, so you probably have a verb anyway. We'll give you a minute to jot down some ideas for I. All right, let's look at the answers here. So before we look at the actual answers, let's go back to the slide that I presented in the previous video. So looking at wetlands, they really do this physical treatment. They act almost like a speed bump, and they slow the water down before it enters into a larger body of water, and that stuff can settle out just like gravity settling out things in primary treatment. It also does a biological process by which these plants, these marsh grasses, absorb nitrogen and phosphorus. So for EI, the answer would be 1 point for physical, mechanical, removing, trapping sediments, solids, objects, particulate through processes such as settling, sedimenting, filtering, and greening. So Ms. Fassler mentioned the fact that planes typically want a verb. There's a great verb there. The secondary treatment is removal of this bacterial or biological action, breaking down and decomposing some of that organic material. So you should see some parallels between wastewater treatment plant and wetland. So let's kind of go back to our visual representation skill. Remember that in the description we read the other day, wastewater treatment was one of the things explicitly mentioned in the skill. And just as a reminder, this will really ask you to look at the pieces and parts of a visual model, then go into how are they related, and then finally what does that model tell you. So it's going to go for simple to more complex. But here's a visual model of a wastewater treatment plant. We'll take 30 seconds and answer this question. All right, so hopefully you were able to see that if that air compressor were to malfunction, we would lose that bacterial action because the dissolved oxygen would not be there for them. The next one I want to look at is FRQ number 1 from 2007. This is a great one all about sewage treatment. So it really asks you to identify primary and secondary treatment, some pros and cons of everything. It was a really great one to practice your knowledge about wastewater treatment. However, I want us to focus on this one, on part E. So if you would, let's read this. It says the final step in sewage treatment is disinfection. Identify one pollutant that's targeted during disinfection and identify one commonly used method for disinfection. So let's take a look at these. I'm not going to ask you to do it now just for time's sake, but you should be able to identify some of the pollutants that we're getting out during disinfection, like bacteria or pathogens or the microorganisms. How do we do that? We mentioned chlorine, ozone, and UV radiation, UV light as one method to do that. So hopefully at the end here you can explain where does your toilet go and where does your trash go, and really look at the environmental consequence of those things and how the structures that we build, a modern sanitary landfill and a wastewater treatment plant, work to address those. Thanks for watching, and I will see you next time. Bye-bye.
Hi, APES students. Welcome back to the College Board virtual lessons. We are going to wrap up Unit 8 on aquatic and terrestrial pollution today. I'm Ms. Fassler, coming to you from Marshfield High School in Marshfield, Wisconsin. Let's take a minute to go over the lesson that you looked at with Dr. Sowell yesterday. If you think back to the last week and the topics that we covered throughout Unit 8, we sort of had this theme of here are different ways that pollutants enter an aquatic ecosystem. Here's the impact they have on ecosystems and on human health, and hopefully some solutions we'll take a look at for how we manage some or mitigate some of those issues. So yesterday, Dr. Sowell did a really nice job of sort of bringing this full circle for us by showing us 2 different ways that human societies manage different kinds of waste. We have solid waste that goes into a landfill and has implications for impacting aquatic ecosystems, and then since I drink water, could impact human health. And we also looked at sewage treatment and how wastewater is treated to prevent us from coming in contact with harmful substances. So let's kind of get our APES brains rolling here again by taking a look at a couple of ideas from yesterday. Explain why wastewater is exposed to a disinfectant prior to discharge. Remember that explain why skill or command verb that they're asking me to use really requires a because. It's for me to provide a reason. So if you want to think about that, explain why wastewater is exposed to a disinfectant. And one of the main reasons that wastewater is disinfected is because it will kill disease-causing bacteria. And that's pretty cool because we're going to look at some of those disease-causing bacteria today and a specific disease that they can cause. The other topic again that you looked at was landfill, what we do with solid waste. So see if you can, in your head or writing on paper, describe a process to prevent contamination of groundwater with leachate from a landfill. Remember, the leachate is that liquid that filters through the landfill and can potentially contaminate groundwater. So describe a process to prevent that. And one of the things Dr. Sowell talked about was how they put a clay liner or a clay layer, they compact it down below the landfill because clay has a very low permeability. Therefore, that leachate is not going to easily get through that layer of clay and get all the way down to the groundwater. So let's take those ideas and carry them forward to our lesson today. We have 4 different learning targets that we're going to look at, 812 through 815. And again, this will wrap up Unit 8 on aquatic and terrestrial pollution. I have 2 big objectives today or goals I would like us to accomplish, and that's to be able to use a dose response curve to imply what that data means about an environmental issue. So these 2 learning targets, this is just a definition of what we mean by this term lethal dose 50 or LD50. We represent that kind of data on a dose response curve. We'll briefly mention pollution and human health and then spend a fair amount of time looking at pathogens and infectious disease. So we're going to look at that dose response curve, and then we're going to make this connection between a lot of different things we talked about in environmental science, how humans interact with the environment, and how that's leading to a spread of emerging infectious diseases. 2 big science practices that we'll use as we go through and accomplish those objectives. Number 1, scientific experiments. And I'll show you the skills that are sampled under that, and finally environmental solutions. We'll deal with a couple of those specific skills. So let's go ahead and get started with those first 2 targets, which were, again, what is lethal dose 50? It's defined as the dose or concentration that will kill 50% or be lethal to 50% of my test population. So we're going to look at some examples of that. And then, as I mentioned, that data is represented on this dose response curve. And so I want to make sure that I know how to read and interpret that and then be able to apply that to understanding some other environmental concept. Here are the specific skills within the scientific experimentation science practice. Notice that on the exam, you are not going to be assessed on making observations or collecting data. You won't do an experiment. You just have to be able to realize the components of a good experiment and perform the following skills. Identify identify a testable hypothesis or scientific question for an investigation, and then identify and describe different aspects of that research method or design or measure that you use. So let's take a look at some data and make sense of that science practice. Here's a dose response curve. First of all, this is just a kind of a generic example of a dose response curve. And remember that I-squared process when I look at data represented quantitative data represented in a graphic form. I want to identify what I see and what I know about that graph, and then I want to interpret it. So we start off with our dependent variable, always on the x-axis. That's my dose. That's how much of whatever pollutant this graph is representing, how much I was exposed to. If you looked at a bottle of ibuprofen, it would list a dose for you. Here's how many pills you should take, and that's probably measured in milligrams. That's my unit. Now, when you look at that label, it's probably going to say, oh, if you're under 3 years age, maybe you don't even take this, or 6 to 10 years, and they have different age categories, which really has a lot to do with the average size of a person in that age category. So we will sometimes see this x-axis represented as milligrams per kilogram of body mass. In other words, what might be a safe concentration for a 60 kilogram adult would not be a safe dose or concentration exposure for a 15 kilogram child. My y-axis, my dependent variable, is identified here as response. This is the percent response, and oftentimes we see that y-axis represented as actual percent mortality. So I've identified a lot of what's going on here. Now, how about the interpretation? I can see that there is a positive or direct relationship between dose and response. As I increase the dose, overall, there is an increase in response, an increase in mortality. The other big thing I want to interpret from this is to actually read it and identify the LD50 value. What dose or concentration will kill 50% of the test population? So what I do here is I go up to my 50% on my y-axis, and I read over to where that intersects my best fit line. Each of these is my data point, and then I put that line of best fit on there, and then I read down and I see that my LD50 is 20 milligrams. So now let's take a look at how we can put this into practice for an experimental design scenario that a lot of APES students go through and do in their classroom. We're going to tie the process back to a concept that you learned about, again, back in Unit 5 on land and water use, where you learned about different irrigation methods, and that sometimes when I irrigate a crop, even if I'm pulling that water, pumping it up from the ground for a center pivot irrigation, or if I'm withdrawing it from surface water, maybe that has been diverted from a river, there's naturally salts dissolved in that water, and as I irrigate with that water, and the water evaporates, it leaves the salts behind, and over time, that can be toxic to plants. Really, anything can be toxic in a large enough concentration. So the common lab that students do to demonstrate this idea is they perform what we call a bioassay. That's just an experiment where I'm going to expose a tissue or a living cell. In this case, we're just going to use a seed of a radish plant. We're going to expose it to different concentrations or potency of that chemical to see how it reacts, to see the mortality. So here's our question. Remember, we want to be able to pose a question or hypothesis for research for an experiment. And in the FRQ, they may present us with a little bit of a background or scenario, kind of how I refreshed your memory about salinization, and you could then pose your own question. Maybe they're going to show us a data table or graph of something from an experiment and ask you what was the question that these researchers were asking. So to get you kind of used to this, I'm going to give you the answers right away, and then you can try one on your own. So my students asked the question, how does salt concentration impact the germination of radish seeds? And their hypothesis, because they already looked at that LD50 curve, was that increasing concentration would increase the toxicity. Let's next move into the, so hopefully that first part of that scaffolding, that skill, the first skill in that practice is pretty straightforward. Identify a research question or hypothesis based on a written scenario that you're given or some type of graph or diagram or chart. The next part, identifying and describing my research method and design, and kind of walk you through the criteria that my students used in this lab on salinization to demonstrate what we mean by that. So the first thing they did was they had 10 little petri dishes, 10 little chambers that their seeds were going to go in, and each petri dish corresponds to a different concentration of salt solution. So the big idea there is that I have a number of different treatments. And when you describe a research method or design, you always 10 might be a little much, but you want to have a pretty fair number of different concentrations. Let's say, for example, a student did this experiment and had 1% salt concentration and 10%, and they saw that at 1% all the seeds germinated, and at 10% none of them did. Well, they don't get very precise on really dialing in on what concentration was actually harmful because there was such a span. They only had 2 different test groups or 2 different treatments. So in this example, the students had 10 different treatments. Each petri dish had 10 radish seeds. You can see that they've counted them out. That's the idea of a replicate. If, for example, they only put 1 seed in each concentration and that seed didn't germinate, they would conclude that concentration was toxic. But what if I just had a dud seed? What if there was a bad seed in my little bag that I bought and that seed never would have germinated no matter what? So I want to replicate or have a number of different test samples at each concentration, and then I can average those results. Next, each of the seeds received 2 milliliters of the concentration of salt that they were exposed to. So they had increasing concentrations of salt, but all of them got the same quantity of solution, so that was not a variable that would impact the outcome of their result. That could be a whole different variable. How does the quantity of salt solution impact the ability of seeds to germinate? So they kept that as a constant, a variable that did not change throughout their experiment. In addition to that, they stored them in a cool, dry place for 4 days, and then they measured the length of the root in millimeters. So you can see here, they actually measured 2 things. First of all, they simply counted, did the seed germinate or not? They considered it mortality or death, if you will, if the seed did germinate. We'll look at that data in a minute. So they counted how many seeds germinated out of 10 in each solution concentration, and then they wanted to know, back to that idea of range of tolerance. Even if the seeds basically germinated, maybe they weren't as successful. Maybe they weren't able to thrive and grow and be as successful in higher concentrations. So the second part of their data was to measure this little, it's like a little embryonic root as those seeds germinated and average that. So let's look at the 2 different kinds of data that they collected. First, their salt toxicity data. We have our independent variable. Remember, I control the independent variable. Students mixed up different concentrations of salt from 0 to 3.5%. We have the dependent variable. How did those seeds respond to that? And remember, we simply counted out of 10 of them, how many of them did germinate? That was mortality. They then had to interpret that. So they drew a nice best fit line through their data points, and then they had to interpret it by reading or determining the LD50. Remember how we did that? This is a common practice, whether or not we're looking at an LD50 graph or a different kind of graph, that you might be asked to identify a certain value off of one of your axes, provided the data from the other axis. So if I know that LD50 is the dose or concentration that will kill 50%, I read over to where that 50% intersects my line and read down, and I see that the LD50 of salt for radish seed germination is 1.75%. In other words, at a concentration of 1.75%, 50% of the seeds would not have germinated. Now, the next thing we want to look at in terms of describing our research method and design, I'm going to give you a little practice in doing this. Here is a graph of the data that represents the average root length. Remember how they measured those. So I'm going to give you a minute. You can either write it out or go and put it on a piece of paper and see if you can answer these 4 questions. What is the independent variable? What is the dependent variable? What is the experimental control? This is not something we've addressed yet. This is not a constant, like 2 milliliters in each petri dish. fish? What is the control? And finally, can you identify one other aspect of good experimental design? Why don't you take a minute and look at those 4 questions? Well, the first 2 should have been pretty easy because it's the same experiment. So the independent variable is always the x-axis. That's my salt concentration. Remember, that's the variable that I am manipulating or controlling. I independent, I control. The dependent variable, what is responding to a change in salt concentration? That is the length of the root. Anybody get the control? When I look at this, I can see that I exposed some of my radish seeds to 0% salt solution. So here's the purpose of the control. Students often confuse control and constant. Constant is something that is held the same. The control is always a test group, a treatment that is not exposed to the independent variable. Again, let's say, for example, I set up this whole experiment and I go to read my results 4 days later and I didn't have a control. I did not have that 0% solution. And I found that none of my seeds germinated. Well, I would conclude that there is no threshold level that is salt that is safe for radish seeds. They have a very narrow range of tolerance. Any salt at all is going to kill them. Well, the purpose of the control, which in this case was distilled water, it had no salt in it. If my control group, I would assume based on my question and hypothesis that water with no salt is not going to be harmful or toxic to my radish seeds. So if my control group did not have any seeds germinate, I could tell that there was a flaw in my experimental method or design. So I always want to make sure that I have that control group, a test group that is not exposed to the independent variable. And then again, we just talked about a number of those other aspects of good experimental design. I want a number of different treatments. And we're going to talk about this more in a couple other units that'll make more sense to you. I want to have more than one test subject per treatment, and I want to make sure that I have constants. The next learning topic in this unit, topic 814 on pollution and human health. So you look at it, it's pretty straightforward. Oopsie. The main part of this is really looking at a couple of specific different diseases that are related to untreated sewage and to asbestos. We're going to talk about dysentery a little bit. Dr. Sowell really kind of hit that learning target in talking about untreated sewage, and we'll come back to that in a minute. And then Dr. Sowell is going to talk about ozone tomorrow. So you can talk a little bit about some of those respiratory problems tomorrow. One of the biggest ideas here is this idea, we call it synergism or a synergistic effect, that it's really hard sometimes to isolate how one pollutant impacts me because I'm exposed to so many different pollutants. A common example you could think of is, mesothelioma causes lung cancer. And I also know that if I smoke cigarettes, I have a greater risk of developing lung cancer. If I both work in a field where I'm exposed to asbestos and I smoke cigarettes, how could I isolate which one of those risk factors was actually gave me lung cancer? Another really good example of that is back to our idea of persistent organic pollutants, particularly different kinds of plastics, because we are exposed to so many different kinds of persistent organic pollutants, and many of them have the same type of disruption to the endocrine or reproductive system or nervous system. It's oftentimes difficult to isolate exactly which of those pollutants I was exposed to that caused the impact or effect. So the next thing we want to do then is take a look at a sample practice question from a released exam, a multiple choice question that really deals with experimental design. So take a second and look at this experimental design using mung beads and ammonium sulfate and see if you can select the correct multiple choice response. So this is one of those questions where I have to pick out if there's more than one statement that is true, and indeed there is. The choices 2 and 3 correctly identify the independent and the dependent variable. Half of statement 1 was true, that the control group would have no ammonium sulfate. Remember, the control is not exposed to the independent variable that I'm assessing. Obviously, there needs to be seeds or it would be much of an experiment. Okay, let's go on to the last learning target then in this section on pathogens and infectious disease. It's a very timely topic because we're dealing with virtual instructions at home because of the outbreak of a very infectious disease. So let's look at a few of the specific knowledge statements that are contained within the learning target 815. Poverty-stricken low-income areas often lack sanitary waste disposal and have contaminated drinking water supplies, and thus are havens for infectious disease. Remember, dysentery was one of those infectious diseases that is specific to our curriculum that is associated with drinking contaminated water from a contaminated supply. Oftentimes, we see maps that show how diseases are being spread from equatorial climates northward and southward from the equator as climate change causes they have a range of tolerance for temperature, but as climate change changes temperature, we see that those ranges are often expanded. And understand that this could have to do with the range of tolerance for temperature, either for the vector that spreads the disease, we're going to look at vectors in just a minute, or for the pathogen that vector is actually transmitting. You're going to see that'll make a lot more sense to you in a minute, so we'll come back to that. And actually, we'll really look at this in a little more detail on Thursday when we look at impacts of climate change. We're going to use Zika virus. Zika virus is specifically an infectious disease specifically mentioned in our central knowledge statement. It's also just a really good case study to tell the story of how vectors spread infectious diseases in general. Pathogens will adapt and take advantage of new opportunities to infect and spread through human populations. We're going to use an Ebola case study to really address those last 2 essential knowledge statements. Again, the process is very global. So even though they give me a couple of different specific pathogens in my essential knowledge statements, once I understand vector disease transmission, they all work in kind of the same way. And once I understand a zoonotic disease or how a disease gets transmitted from an animal to a human population, they all work in generally the same way. The processes are transferable for our purposes. So let's take a step back for just a second and come back to this idea that's kind of been a theme throughout this unit is pathway of exposure to different kinds of pollutants. And in this case, what's our pathway of exposure to these infectious disease organisms? So we already talked about dysentery and how I could get dysentery from untreated sewage. I just mentioned that Zika virus is transmitted by a mosquito, by a vector, that some wild animals carry viral disease pathogens, disease-causing organisms that can be transferred to a human population. And then certainly the implication of a pregnant woman being able to transmit that infectious disease organism to her unborn child. So let's take just a minute and look at a case study of Zika virus, a vector-borne disease, and then we'll go back and dig into some of those essential knowledge statements.
Throughout the Americas, mosquito bites are tied to many viral outbreaks. In the months before Zika spread in Brazil, chikungunya, a tropical virus that causes terrible joint pain, invaded the Western Hemisphere, infecting almost 1 million people. And West Nile virus sickened more than 2,000 victims in the U.S., with symptoms ranging from fever to paralysis. In South America, the Zika virus is spread by a mosquito called Aedes aegypti. Other diseases, including dengue, chikungunya, and yellow fever, are also spread by this persistent insect.
Aedes aegypti is the cockroach of mosquitoes. It lives indoors and outdoors. It bites daytime and nighttime. It develops resistance to insecticides easily. The eggs can overwinter for a year. To control it, we have to kill the adult mosquitoes, the larval mosquitoes, both inside and outside.
health officials have used sprays and screens to protect people from diseases spread by mosquitoes. Throughout the Americas, mosquito bites.
Sorry. So one of the big ideas that kind of emerged there is that we know already that mosquitoes are our strategists, and they provide a lot of characteristics about the mosquitoes that make them such a good host organism for spreading that pathogen. Again, the mosquito is the vector that is transmitting the disease-causing organisms. But because mosquitoes are our strategists and reproduce so quickly, it's really easy for them their population to spread disease very rapidly. So let's do a little guided practice on kind of that big idea. I'm going to walk you through this practice number 7 on environmental solutions. And we're going to take what we just learned about Zika virus to demonstrate how this practice is scaffold. First, describe an environmental problem. Well, one environmental problem we saw is that mosquitoes are vectors that are tied to viral outbreaks that spread infectious disease. Some potential responses or approaches to solving that problem. We saw that they showed me in a little video clip that one of the things they do is spray a pesticide. They also mentioned using nets, but we're going to focus on spraying the pesticide for just a minute. And then the next part of skill that is associated with this practice is be able to describe disadvantages, advantages, or unintended consequences of that potential solution. So take a second now and see if you can answer that third part. We know that mosquitoes are vectors that spread disease. We can spray a pesticide to kill that mosquito to slow the spread of the disease. Can you identify a disadvantage, advantage, or unintended consequence of spraying pesticides? So there's a couple of different things you may have focused on. Remember, we looked at DDT as a persistent organic pollutant. And so one of the drawbacks or disadvantages or unintended consequences is that humans could be exposed to that pesticide and suffer neurological problems. It could disrupt neurological development or function. And the other big idea is coming back to that idea of the pesticide treadmill and pesticide resistance. That the pesticide is kind of like a quick fix, and it may, cause a quick reduction in my mosquito population. But remember the idea of natural selection. There may naturally be some mosquitoes in that population that have a certain little binding site on their cell where that DDT, that persistent organic pollutant, has to bind to initiate its neurological impact. And if there's randomly a mosquito that has a little tweak in that receptor site on its cell, maybe that DDT can't bind in there and it's not going to kill it, and it survives, reproduces, and passes on that beneficial trait. Next, we're going to take a look at a second quick little case study. In this case of Ebola. Remember, this is an example of what we would call a zoonotic disease, or a disease that is transmitted from an animal to a human population.
Ebola outbreak in West Africa is believed to have started sometime in late 2013, with sort of cases coming up in a village in India. The epidemic started when a bat came in contact with a human, and the virus passed from that animal to the person. Sierra Leone and Liberia are just recovering from some very brutal civil wars. 85% of the health clinics in Sierra Leone were destroyed during the civil war, and West Africa has a very high population density. They have some very good roads. So if you take a health system that's in shambles, and you had an Ebola outbreak and a rapidly moving population, then you have the perfect storm.
So let's kind of look at the big takeaway about these emerging infectious diseases. And I'm just going to mention COVID-19 a little bit, since it really is another case study or example like Ebola. Remember some of those essential knowledge statements that we looked at. It's how humans are interacting with their environment and contact with animals that may have these viruses. So we learned in our ecology unit on population about these different resistance factors. Remember that disease is a density-dependent resistance factor that's going to control the population. So the greater my population, the more rapidly that disease is going to spread from one organism to another. Back to this idea of natural selection in two aspects. Number one, that virus can mutate. If you look at many viruses, again, it's not all the same, but the process is somewhat transferable to many different zoonotic diseases. And the Ebola virus kind of looks like this, and the HIV AIDS, and even the HIV virus, the human immunodeficiency virus that causes AIDS, kind of looks similar. So these are all proteins on the surface of the cell that has to bind on the host cell organism to be able to open up the cell to begin to membrane and kind of get inside of it and take over that host cell machinery. Well, if I have a virus that mutates rapidly because they're replicating a lot and there's a lot of transfer mutation in that replication, then they may be getting a beneficial trait. What would be a beneficial trait to the virus? Something that would make it even better at binding on my host cell and being able to get in and infect me. This is just a really good example of what Darwin meant by survival of the fittest. It's not the strongest or the best looking. It's the genetically fittest. That virus that randomly got a mutation that made it more efficacious, more virulent in binding and infecting host organisms. Another application of natural selection is that some individuals in the population may have a natural immunity. I'm not necessarily stronger than the next person that doesn't have the immunity. I just happen to randomly get some little tweak when my DNA was copying that gave me the ability to fight that off. And you hear a lot of research with COVID-19 now kind of looking at that natural immunity. People that have gotten the viral, been infected by the virus and have recovered, and now can we tap into their immune system to help people that have not developed that resistance to it. And the other big idea is how humans interact with their environment. That you may have heard this term novel viruses. To be clear, the Ebola virus, the HIV virus, the COVID-19 virus, none of these are new viruses. They're new to us. They've been present in that wild animal population. Maybe in the case of Ebola, we believe a fruit bat, but maybe that virus has been in that population for millions of years. And through natural selection, that population has developed an immunity, and maybe it kills host organisms in low numbers that don't have that immunity or have a compromised immune system to begin with. But for the most part, those viruses have those animal populations that kind of learn to live with these viruses over a long period of time. So that really brings us to what an exciting field of environmental science this is. One of the researchers that you heard speaking in the video was a disease ecologist, someone who works with the ecology of the disease and how it is transmitted through different populations. So this is just all of environmental science coming together. It's looking at cultural practices and ecotourism and how I may go to kind of a wild place because they have ecotourism, and I may bring a virus back with me. Our practices on how we raise animals. If we are raising livestock or other domesticated animals in close proximity to where we as humans live, we could be getting exposed through livestock animals. Certainly international trade, urbanization, as people move into urban areas and we increase the density of a human population. And then some of these extrinsic factors, things like habitat loss. As we increase the rate of deforestation and encroach on habitat of wild animals, we are exposing ourselves to viruses that they have evolved with, that they have learned to live with, but that are new to us. So there's agriculture practices. There's all of these different ways that humans interact with their environment that is increasing the spread of infectious disease. Certainly one of the most poached endangered animals in the world is the pangolin. These are illegal. These are pangolin scales that are being traded. They're scales that have perhaps been confiscated. And we're going to talk about that a little bit more when we look at endangered species and some of the things that we can do to prevent that. So let's take a quick check for understanding to see if you got that big idea through a multiple choice question. Factors that increase the spread of infectious disease include all of the following except. And this one's pretty straightforward. Obviously, the infectious disease are not spread by chemical toxins. And I think we kind of talked about all of these. Remember, we'll come back to the global warming one in the next in a couple of days. So let's take a look at an AP exam practice question. This has appeared on a released AP exam. So the wording is exactly how you would see it on there. And I selected two parts of the prompt for you to take a minute and try and write. Diseases can devastate populations. However, diseases do not drive their host to extinction. Provide one explanation for why diseases seldom cause extinction, and then provide a likely reason for the increase in emerging infectious diseases. Include an explanation for your reasons. That's kind of a two-part one. Let's just take a couple minutes and look at that. You can write it out or think about it in your head. Let's see how you did with this first one. That's what I had kind of just talked about. So hopefully that made sense to you. We've got genetic diversity in our wild population in order to enable some of them to survive and reproduce. The idea of coevolution is something you may have talked about in your unit on natural selection, that maybe that host organism that's infected, like the fruit bat, and the viral organism have kind of co-evolved that they can both figure out a way to survive. This is one we didn't talk about, but maybe some of you would have picked up on from previous units in environmental science, that that disease, if that disease organism kills all of the hosts, then it's not going to have any hosts left to invade, and it can't survive. That virus can't survive outside a host organism for very long. It can't reproduce outside its host organism. And that whole idea of density, that once a disease goes through and lowers the population, there's less population density, so less organisms to impact. A likely reason for the increase in emerging infectious diseases, and again, we talked about a couple of these and the explanations for them. Again, really a lot of it all comes back to how humans interact with their environment. And as we kind of wrap up for today and wrap up Unit 8, this field of infectious diseases, public health field of infectious disease, really is an exciting area of environmental science. And as you can see here, we need public health workers that have a background in veterinary medicine or veterinary health, because there are diseases that are transmitted from livestock to humans. So I need people that understand the ecology of veterinary organisms. I need wildlife ecologists. I need people that understand my deer population or other disease organisms that can be impacted from wild animals, and certainly people that work in the field of human public health. So tomorrow, Dr. Sowell is going to come on and talk to you a little bit about ozone depletion. We're going to be moving into Unit 9. Remember, Unit 9 is still a unit that we're covering so that you get the full scope and sequence of your AP Environmental Science course. And we'll make some real good connections back to previous content and previous skills that you need to know. So tune in tomorrow. I do want to mention that if you liked that little snippet that I gave you about Zika virus and Ebola, those are both videos produced through the Howard Hughes Medical Institute, and the links for the full length, they're each only still about 8 minutes, but the links for both of those YouTube videos are provided for you. So go take a look at them and do a little bit more exploring. I will see you next time. Have a good rest of your day.
Hi, everybody. Welcome back to our online virtual lessons for AP Environmental Science. My name is Dr. Sowell, and I teach APES here in Jacksonville, Florida at Darnell Middle High School. So just to warm up, normally we would warm up with kind of a question or a refresher from the last lesson, and Ms. Fassler did a phenomenal job talking to you about pathogens and human diseases, as well as LD50 and the great experimental design stuff associated with that. But because we're starting Unit 9 today, I thought we would take a second and just look at what Unit 9 is about. So I want to highlight one particular word here. So it says a central aspect of environmental science is to understand the global impact of local and regional human activities. Humans can mitigate their impact through sustainable use of resources. So I just want to highlight that word mitigate. Most of you probably already know this, but just to make it explicit, it just means to make less harsh or less severe. And so the whole point of Unit 9 is to take these big system thinking ideas and understand them in light of everything else that you've learned in the course. Some of the stuff in Unit 9 you probably at least heard of before in terms of greenhouse gases or climate change or maybe ocean acidification. But what Unit 9 does is it allows you to take everything you've learned and put it into context with some very specific environmental issues. So just taking a look at Unit 9, 9.1 and 9.2 we'll discuss today, stratospheric ozone. Ms. Fassler tomorrow is going to look at greenhouse effect and climate change, and then I'll jump back in and go into the ocean with you to talk about ocean warming and acidification. Ms. Fassler will come back and look at two unique categories of species, invasives and endangered. And then finally, I'll wrap up our Unit 9 talking about human impacts on biodiversity, so concepts like habitat loss or habitat fragmentation. So that's the kind of flow of what we're going to be doing over the next couple of videos. So thinking about system thinking, thinking about global change, we need to consider a few things in particular. And I like to use this framework. It's called Understanding Global Change, and it's a resource from HHMI Biointeractive, and I will display the link for that in just a little bit. But in order to understand these big global change ideas in this unit, the first thing we need to understand is how the systems work. How does the biosphere work? How does the atmosphere work? How does the hydrosphere work? How does the lithosphere, the geosphere work? How do each of those little systems operate naturally? And then along comes us, causes of change. Now, causes of change can be human, but can also be non-human as well. So it's nice to understand the system, what we do to the system, and then to be actually to measure changes, measurable changes, quantifiable changes. This is the evidence of those changes. What have we done, both human and non-human causes of change? But again, that idea of understanding the system, what have we done to it, and then what are the measurable effects helps me to think about these concepts. So today we're going to be looking at stratospheric ozone depletion. And if we use this framework, today's lesson really is going to start with how that system works. What does the ozone layer do in the stratosphere? Then we're going to talk about some human activities that change that system, so particularly the use of CFC. And then we're going to look at what are the measurable effects that have resulted from that action. And in particular, we're going to focus on human health effects today. So this is the resource that I was talking about. This is a graphic showing kind of all the details in there. But this is a resource, like I said, from HHMI Biointeractive, and the link is below. And what the resource does, it allows you to build models based on those three categories: causes of change, how the system works, and measurable change. This one, for example, is talking about ocean acidification, something that we'll talk about in a few lessons ahead. But this is a really nice resource if you're looking for a place to practice constructing system models of the ideas and issues that you found throughout the course. So I highly recommend taking a look at it. So where are we going to go today? So we've got two content goals for today. 9.1, what is stratospheric ozone depletion? Number 2, what do we do to reduce that problem, reducing ozone depletion? So nice pairing here. We just got a problem and a solution. And so clearly we're going to practice the practice number 7, environmental solutions, but also we're going to take a look at concept explanation practice number 1. So some prior knowledge to review before we get started. So there are some things that we're going to loop back to today, and it'll be a great review. But if you're not comfortable with these topics, I would suggest taking a peek at them. First of all, the Earth's atmosphere. That's in Unit 4, Topic 4, the structure of the atmosphere. Introduction to air pollution, Unit 7, Topic 1. In particular, we're going to talk about photochemical smog today, and that's coming from Unit 7, Topic 2. So how does the Earth function, and then some specific pollutants that we've been putting into it from Unit 4, Unit 7. All right, so here's what we need to know from 9.1 and 9.2. 9.1, the first goal is by the end of this section, you should be able to explain the importance of stratospheric ozone to life on Earth. First of all, let's talk about our cast of characters here. We're talking about ozone, and that is O3. So sometimes during the presentation, you'll see O3. Sometimes I'll write it at ozone, but you need to be familiar with that. So to get to this understanding of why the stratospheric ozone is important, we are going to, again, review the structure of the Earth's atmosphere. Then we're going to make a clear distinction between stratospheric ozone and tropospheric ozone, that ground level ozone. We need to make that distinction very clear. Then we're going to, once we define those two, we're going to specifically look at stratospheric ozone. What is it doing for us? Then we're going to look at some human actions that have depleted that stratospheric ozone. Then we're going to talk about those effects, those measurable changes that we mentioned before from the model. And finally, what do we do about it? What are some possible and current solutions to combat the ozone depletion that we cause? So as a quick review of our layers of the atmosphere, this was in a prior unit, and basically you really just need to know the layers of the atmosphere and some of their basic characteristics. So we've got troposphere, stratosphere, mesosphere, thermosphere, and exosphere. So to give us a little quick review, it's nice sometimes to hear other words than mine. So we're going to take a look at this clip from the Meteorological Office in the UK. Nice little review of those layers of the atmosphere. I like that because it not only shows you the relative thickness or height of each of the layers, but it also points out some of the unique differences in terms of the temperature gradient that happens within each one of those layers. So now they mentioned it slightly in that video, the ozone layer. That is what we're talking about today. So we've got this thing called ozone, and I want you to think about it almost like an actor. An actor, depending on if he's in a horror movie, might act as a villain, maybe, or he's in a superhero movie and he acts like a superhero. So this one molecule of ozone is neither good nor bad. What makes it good or bad is its location. So I typically talk to my students about ozone being good up high, but bad nearby. Good up high, meaning in the stratosphere up high. Bad nearby, being down near us. So let's break down bad nearby a little bit more. And this should be a review of Unit 7 for you. So in the ozone, or the troposphere, we have tropospheric ozone. One of the things that I always tell my students to do is never to write naked ozone. Always attach it to something. So from this point on, it might be useful for you to always write either tropospheric ozone or stratospheric ozone. That way, just by writing that term, the reader knows which layer you're talking about. So here we're talking about tropospheric ozone down toward us. Sometimes it's called ground level ozone. But this is a secondary air pollutant and it's man-made. So you should realize what the word secondary means, and also that this is not a natural substance. It is one of the main components of photochemical smog, and that, as you recall, is when we have things like NOx and VOCs and sunlight all combining to make this brownish haze called photochemical smog. And the main constituent of that, or one of the main constituents of that, is ozone, tropospheric ozone. And that can clearly lead to a litany of respiratory problems for humans. So down near us, nearby, ozone is bad, but up high it's good. This is our global sunscreen. This is what is blocking out the majority of the UV radiation. Without this ozone layer, this layer of stratospheric ozone, life on Earth as it exists now would make it. So life on Earth, the biosphere, the organisms of the Earth, including humans, have all evolved to deal with the natural levels of UV radiation that make it through the ozone layer. So without the ozone layer protecting us, we would be exposed, and all life would be exposed to more UV radiation, and that would cause irreparable damage. So just as an analogy, think about this as sunscreen. So if you took sunscreen and put it up high, actually on the outside of your body, it's a good thing. So stratospheric ozone and sunscreen are really good up high on the outside. But if you were to eat sunscreen, don't eat sunscreen. But if you were to eat sunscreen, that'd be a bad thing. So just like sunscreen isn't good or bad, it all depends on where it's located. So ozone isn't good or bad, it just depends on where it's located. Is it stratospheric ozone or tropospheric ozone? So first of all, why do we use that sunscreen? We're trying to prevent sunburns. We have some clear skin damage that can result from getting a sunburn. And remember, a sunburn isn't a result of being hot, it's a result of being exposed to that UV radiation. So the UV radiation is coming down, interacting with our skin and causing some damage. So let's take a look at this little graph here. So you can see the troposphere is this lower part and the stratosphere is here in this middle part. And we've got three different types of UV radiation coming in: UVA, UVB, and UVC. There's some distinctions between the two in terms of wavelengths, but one of the most important things to think about is UVA has the least energy, and UVC has the most energy, and that will be the most damaging. But you'll notice this large influx of ozone in the stratosphere, the good up high stratospheric ozone, blocks out the vast majority of UVC, a good chunk of UVB, and only some of UVA. So here on the surface of the Earth, we are exposed to some UV radiation. And if we get too much of that exposure, it can lead to some very specific and significant health impacts, particularly cataracts and skin cancer. So what are cataracts? Cataracts are basically a clouding over the lens of the eye. And you can see this individual in the bottom left. One eye is normal, and the other eye has developed this cataract. And it can result in some pretty significant vision problems, such as blurring. It can be caused by lots of things, but UV exposure is one of those. But again, could impair your vision. In addition to that, we have skin cancer. So most skin cancers are a result of exposure to the UV rays in sunlight. That's coming from the American Cancer Society. So what is that UV light doing to your skin to cause that? Well, it's damaging your DNA. So that UV radiation penetrates your skin tissue, can cause damage, DNA damage, or mutations, which can then lead to skin cancer. So it's definitely something to be cognizant of, and it's definitely something to remind us to wear sunscreen when we're outside. So just as a little review of that sunscreen and cancer risk, let's take a look at this.
It can be easy to get caught out in the sun and get sunburned. But what is sunburn? Sunburn happens when the DNA in your skin cells has been damaged by too much UV radiation from the sun. The heat and pain you sometimes get from sunburn is your body's attempt to repair the damaged cells. The DNA damage can happen before the first signs of sunburn show up, even though your skin may eventually feel and look healed. Some cells with damaged DNA can be left behind because our repair mechanisms aren't perfect. Over time, these damaged cells multiply and can develop into skin cancer. Remember, sunburn doesn't have to be raw or peeling. For people with lighter skin, sunburn may make your skin go pink or red, or it could be irritated or tender or itchy for people with darker skin. You are most likely to burn in the middle of the day when the sun is highest in the sky. Sunburn doesn't just happen on holiday or sunny days. Sunburn can still happen on a cloudy day. Whether you're in the UK or abroad, protect your skin when the sun is strong by using a combination of shade, clothing, and sunscreen.
So life on Earth has evolved to coexist with these normal levels of UV radiation. And when I say normal, I just mean how much naturally makes it through a robust, strong, normal stratospheric ozone layer. But yeah, even with those, or even with that ozone layer, we still have risks. And if we get exposed too much, we have cataracts or skin damage. But that is normal. That is normally to be expected. Now, if we were to get rid of that stratospheric ozone layer, the risks of these things become much, much greater. And so that's what we've done. So now we're going to look specifically at the human impacts to the ozone layer. And that starts with this chemical called, or a class of chemicals called CFCs, chlorofluorocarbons. On an FRQ, you are more than welcome to use CFCs as an abbreviation for chlorofluorocarbons, but you should be familiar with both the word and the abbreviation of the acronym. So here's an example of a CFC molecule. One of the characteristics of CFCs is it has chlorine on it, and that's going to become a key thing in the story of how CFCs harm the ozone layer. So where do we find this stuff? We used to, being a key word, used to find it a lot in aerosols and refrigerants. It was very common to use CFCs to make aerosols like hairsprays and things like that function better, and it was a great part of coolants. So cooling systems like refrigerators would use it. So what is that CFC doing? How is that one molecule CFC taking away our global sunscreen? So what happens is, as soon as that CFC radiation, a chlorine pops off. So we've got now this free chlorine molecule, and that's going to be the villain here in our story, because it combines with ozone and actually steals an oxygen away from ozone. So the chlorine snatches away an oxygen and makes chlorine monoxide and O2. So if we were to stop right here, the story would be bad enough. We no longer have this molecule of ozone that was being useful. It was blocking out UV radiation to the earth. Well, chlorine has just now broken that apart, and we no longer have that one particular molecule of ozone. But here's where the villain becomes even more villainous. So as soon as a free oxygen comes in contact with that chlorine monoxide, it snatches away that oxygen to form O2, and now look what we have back in action, ready to go again, the chlorine. So it can go right back up and do it again. So one CFC molecule could result in the destruction of many ozones because that chlorine is almost recycled to catalyze this thing again. What happens? We have a quote-unquote ozone hole, or more appropriately in the context of APES, stratospheric ozone depletion. So what does that mean? So clearly we have a problem here. We would have a significant effect on the biosphere if the ozone layer, if stratospheric ozone were to be completely depleted. We would have very significant impacts, not only on human beings in terms of skin cancer and cataracts, but if we are experiencing genetic damage to our DNA from that UV radiation, so would other life forms. And so we would have lots of impacts, broad impacts from that. So that's the problem. What's the solution? So in your head, the first thing you should be thinking of, well, if that's the villain, let's ban the villain. Let's ban the use of CFCs. And that is exactly what happened. There was a meeting and an agreement, and we got rid of that evil chemical. Now, so this is really about 9.2. So by the end of this, you should be able to describe the chemicals we've used to substitute for CFCs. So we still need aerosols, we still need refrigerants, we just don't want to use those CFCs. So to get there, we're going to talk about something called the Montreal Protocol, and that is an agreement that bans the CFCs. But we're also going to talk about briefly what are some replacements for CFCs. And just like any solution, we have pros, cons, and unintended consequences. Montreal Protocol. So in 1987, we had an international treaty that agreed on global reduction and eventual phase out of all ozone-destroying chemicals, such as CFCs. And you can see from the graph here, the production of CFCs was increasing. And then we have the Montreal Protocol, and we start to see it drop off. This is an old graph from 1992, so you can assume it's getting lower here. The reason we didn't see an immediate restoration of the ozone, the stratospheric ozone layer, is because CFCs stay in the atmosphere for a very long time. They're very persistent. So although the Montreal Protocol stopped the production of CFCs, we don't expect the stratospheric ozone to repair itself, that ozone to regenerate, for at least a couple more decades toward the middle of the century. So we banned CFCs. It was a great example of an international treaty that worked. Then we had to find something to substitute them with. And so one solution was to use hydrofluorocarbons, HFCs. So again, be sure you know the name and the abbreviation HFCs. It worked fine. It worked fine in terms of aerosols and refrigerants. The problem, HFCs are a strong greenhouse gas. So we know that CH4, H2O, CO2, we have some very clear greenhouse gases that we've talked about in the class before. And now we can add HFCs to one of them. They're not one of the main ones that we typically talk about, but this is an unintended consequence of the solution to ban CFCs and replace them with HFCs. So when we look back at practices, I think this is a great example of this practice number 7, the solution. So we know that this is increasing complexity. When you're asked to describe a problem, describe potential approaches or solutions to that problem, look at the advantages and disadvantages and the unintended consequences, and then use data to select one of those solutions and to justify it. So I want to bring up a very clear misconception in a minute, and to do that, I'm going to ask for the help from this little video clip here, just the last part of it.
15 to 35 kilometers above Earth's surface, a gas called ozone surrounds the planet. The ozone layer acts as a barrier between Earth and ultraviolet radiation from the sun. However, pollution has caused the ozone layer to thin, exposing life on Earth to dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules for every 10 million molecules of air. But it does a very important job. The ozone layer acts as Earth's sunscreen, absorbing about 98% of damaging ultraviolet or UV light. But the ozone layer has gotten thinner. Chemicals called chlorofluorocarbons, or CFCs, are the primary culprits in ozone layer breakdown. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin patch, with the thinnest areas near the poles. The ozone layer above the Antarctic in particular has been impacted by pollution since the mid-1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the northern hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.
So I want to at this point, so hopefully that was a good review, that you should be able to at this point explain stratospheric ozone layer, its function, how we depleted it by the use of CFCs, and how the Montreal Protocol solved that problem for the most part. But I want to point out a very common misconception is that stratospheric ozone depletion is not the same as global warming and climate change. Because they're both dealing with the atmosphere and because there's some chemistry involved in both, sometimes students will implicate ozone depletion as part of climate change. But the depletion of the stratospheric ozone layer is not a direct cause of climate change. They're two different problems. And in fact, if you think about stratospheric ozone depletion, it's a problem that we solved. We found the culprit, we banned the culprit, and we're monitoring the regrowth of the ozone layer. So this is a problem solved. This is a problem we're clearly in. But while they do have some interrelated components and characters, stratospheric ozone layer is about UV radiation, think sunburn, whereas climate change is about heat being hot. So they're related, but they're two different issues, and you need to keep those very separate when you're talking about them on FRQ. So this little last clip talks about the difference between the solution that we've made with stratospheric ozone layer and the continuing problem of climate change.
Humans have started to do the right thing in order to convert the chemical nature of the atmosphere back toward what it was before industrial revolution started.
It'll be some time before scientists can absolutely confirm that the ozone hole is actually growing over, but the signs are good. Unlike that other global problem, climate change. People in the Himalayas struggling this week against the sort of weather scientists say will get worse as carbon dioxide levels increase. It's so much more difficult. Our cars, homes, factories all contribute to heating the planet. This problem may not get solved at all. Roger Harridan, ABC News.
So clearly I'm a little bit more optimistic on that lesson, as I think that we can solve this problem, and I think by understanding what this course can tell us, we know what we should be doing, or what we hopefully will be doing in the future. So let's do a quick check for understanding with some multiple choice questions, and then we'll do a quick summary, and then jump into a practice FRQ on this topic. So the question says, the main environmental effects of ozone depletion could include all of the following except. So I'll give you 30 seconds to chew on that. All right, hopefully you realized it was B. Everything else you can see is an increase in ozone depletion would be an increase in UV radiation hitting the Earth, and all of these things are in the biosphere that would be impacted by that, except for a decrease in CO2. Next question says, which of the following human activities is most closely associated with the depletion of the stratosphere ozone layer? So take 27.25 seconds and put out. And the one that should stand out to you is refrigerators and air conditioners, because we implicated refrigerants is something that contains CFCs, and so when those are disposed of, and particularly when they're disposed of improperly, those chemicals can escape into the atmosphere. This next one says, which of the following substances is released by CFCs and catalyzes a chain reaction that breaks down ozone in the upper atmosphere? Hopefully you remembered our villain here was chlorine. The chlorine atom pops off of that CFC as soon as the UV radiation, the UV light hits that. So let's debrief and summarize where we went. So we talked about 9.1, stratospheric ozone depletion, and 9.2, reducing that depletion. So let's look at the specific essential knowledge statements from 9.1. So the first one talks about why the ozone layer is important for life on Earth. We've evolved along with that ozone layer. Then we talked about the CFCs, implicating them in the anthropogenic destruction or depletion of the stratospheric ozone layer. I do want to point out that it says natural factors such as melting of ice crystals in the atmosphere at the beginning of the Antarctic spring. So there is some natural degradation of stratospheric ozone that occurs naturally, but what we're focused on in particular today was the anthropogenic factors like CFCs. And what would happen if this depletion continued? We would have decreased or increased rates of skin cancer and cataracts in humans. So basically, because we know all this, we should be able to explain the importance of the stratospheric ozone to life on Earth. And if you haven't really looked at some of these unit guides yet, you should realize that these are the essential knowledge statements that you should know in order to do this thing, in order to explain the importance of stratospheric ozone to life on Earth. And then for 9.2, talk about the replacements, the HFCs, and some of the pros and cons of that. So based on that, we should be able to describe the chemicals used to substitute CFCs. All right, so let's do some practice here. So we're going to do an FRQ that's going to require some concept explanation. So just remember that this is science practice number 1, and this is asking you to write explanations that describe environmental processes. And your written descriptions should demonstrate that you've done more than just memorize the facts. It's one thing to memorize what a CFC is. It's another thing to be able to explain the role of CFCs in stratospheric ozone depletion. I always joke that my Nana might be able to talk about pollution in a general sense, but she wouldn't sound like she's taking an APES course. You need to sound like you've taken an APES course when you write FRQs. So again, to explain a concept, you kind of describe first, and then you get into more of an explanation. But if you see the word explain, like Ms. Fassler said, be thinking what verbs can you use in your writing, multiple sentences, things like that. So here are our task verbs that I've mentioned every time so far. The 3 that we're going to look at today are describe, explain, and identify. All right, we are going to do the 2013 FRQ all about ozone. We're not going to do the whole thing, but we're going to do some big chunks of it. So in fact, we're going to do everything but B. And we're going to do it in pieces because I think it would be a little awkward if I just said, okay, take 15, 20 minutes and go write by yourself. So we're going to take it in chunks, take a minute or two for each one, and go over the answers. So the prompt says, and actually let me go back one, sorry. Ozone, O3, is an atmospheric trace gas that occurs naturally in the stratosphere. Okay, we know that. It is also formed as a consequence of human activity in the troposphere immediately above Earth's surface. So those two sentences describe good up high, bad nearby. Sunscreen good on the skin, sunscreen bad on the stomach. The location of ozone in the atmosphere determines whether the gas protects or damages the environment. All right, so let's take a look at A. A says identify the type of solar radiation that is absorbed by the stratospheric ozone and describe when human health benefit that results from the absorption of this solar energy. So take a minute or so and we will look at the answer. Okay, so again, there's 2 parts to this FRQ, so be sure, let's look at both of them. So the first one says, identify the type of solar radiation. So you get 1 point for identifying ultraviolet radiation, UV, UV, UVB, or UVC. So that's 1 point for just identifying ultraviolet radiation. Your second point comes from the benefits of that, the human health benefits of being very specific about humans. So that is causing less skin cancer, less sunburn, less eye damage like cataracts. So what is it blocking and what is that benefiting us? All right, C says, the Montreal Protocol of 1987 provided a global framework to phase out CFC production and use. Although the Montreal Protocol has led to a dramatic decrease in CFCs released into the atmosphere, stratospheric ozone destruction has decreased only slightly. So I says, explain the process by which CFCs leads to the destruction of stratospheric ozone. You may use chemical equations in your answer. So this may, you don't have to. So take 1 minute and see if you can describe on your paper, explain on your paper how CFCs destroy the ozone, stratospheric ozone. Okay, take a couple more seconds. So this is a really great example of the difference between being able to identify something and explain something. You may remember that CFCs were involved somehow, but can you explain it? So here's what we were looking for. This is worth 2 points. 1 point for a correct description of how the decomposition of CFCs. So the first point comes from UV radiation hitting the CFC and popping off the chlorine. So absorption of UV radiation by CFC molecules releases chlorine atoms, or you could have represented that with a chemical equation. So that's the first part. The CFCs becoming liberated, or the chlorine becoming liberated from the CFCs. The second point comes from being able to describe that free chlorine now breaks down ozone molecules, or you could have represented that as an equation. Okay, so 2 points there. All right, let's go to the next one. So CII says, explain why the rapid decrease in CFC emissions has not led to similarly rapid decrease in the destruction of ozone, stratospheric ozone. So take 30 seconds and think about that. All right, so hopefully you're thinking about the persistence of the CFCs. That's what I think of. So this is 1 point can be earned for a correct explanation, linking the absence of rapid decrease in the destruction of the stratospheric ozone with one of the following. So you may have talked about how it takes a while for the CFCs to get up into the stratosphere, or the long lifetime of CFCs, or chlorine in the atmosphere, or the continued release of other ozone-depleting substances. So I would probably tend to hit this middle one in my brain, that these persist a long time. So even though we stopped it on a Monday, on Tuesday there's still some up there. And finally, we're going to now go from good up high to bad nearby. So it says, identify a human activity that leads to the formation of tropospheric ozone as a secondary pollutant, and explain why tropospheric ozone levels peak in the daytime. So this question clearly has 2 parts. I recommend to my students, there's no need to restate the question, but you could say one activity that leads to the formation of tropospheric ozone is, and then identify, period, and then go into your explanation of why it peaks in the daytime. So take about 40 seconds or so and jot down some ideas of what you might put for 3D. All right, so the human activity, now it's asking for a specific human activity, not just things in general. So anytime we burn fossil fuels, either motor vehicles or electric power generation, we're putting those emissions into the air and releasing VOCs by doing something like pumping gases or using paints. Why does it peak in the daytime? Because sunlight is involved. This is a photochemical reaction. It's chemically started up. So we're looking for that sunlight answer there. And finally, E talks about the human effects, the negative health effects. Identify one ecological impact and one human health effect. So ecologically, you could talk about it damaging plant tissue or inhibiting photosynthesis. And then for humans, it is the irritation to the respiratory system, coughing, decreasing lung function, irritating eyes. So there's some clear ecological, meaning non-human, and then human impacts as well. All right, that's stratospheric ozone layer. Hope you enjoyed it, and I will see you next time. And don't eat sunscreen. Bye.
Hi, APE students from all over APESlandia. Welcome back to the College Board virtual lesson for AP Environmental Science. We're going to continue where Dr. Sowell left off with the introduction to Unit 9 on global change yesterday. My name is Ms. Fassler, and I teach at Marshall High School in northern Wisconsin. So let's take a few minutes to kind of go over the wonderful introduction to Unit 9 that Dr. Sowell presented yesterday and make some connections between stratospheric ozone that you talked about and the greenhouse gas effect and what happens when greenhouse gases increase in concentration. Just to reiterate, we're really excited that you guys are engaging in some of this material from Units 8 and 9 and making connections to get that really big picture of how these important topics in Units 8 and 9 relate back to Units 1 through 7 and some really good strategies for how you can proceed with the exam from here forward. So back to stratospheric ozone and this big idea of global change. With Dr. Sowell yesterday, you spent a lot of time looking at models and images and making sense of them, and we're going to take that great foundation that you laid yesterday and really add to it. So yesterday with Dr. Sowell, you guys spent your time up here in the stratosphere, and you were looking at the importance of that stratosphere, the stratospheric ozone, and the benefit that it provides for both the ecological and human health, and we could say economic standpoint. Today we're going to spend a lot of our time down here in the troposphere, that layer of the earth that's layer of the atmosphere that's closest to the surface of the earth. Before we dig into that too deeply, I want to take a step back and look at this model of the electromagnetic spectrum. It may look familiar to you. You may have seen it in physics class or in chemistry when you did that electron emission spectra, maybe a flame test, and you talked about this idea of Roy G. Biv. Well, we're not going to get too deep in the weeds here. I'm not going to expect you to explain a process. I just want to kind of make sure that you can identify a relationship and make a connection between these different forms of energy. So yesterday, Dr. Sowell, the kind of big idea that you looked at is what is the importance of stratospheric ozone to life on Earth? And now that you see this electromagnetic spectrum, you're like, oh, that's right. That stratospheric ozone is really important because it blocks incoming UV radiation, different forms of UV, UVA, UVB, UVC, depending on their wavelength. But kind of at the heart of it, that's why we said it was important. And what we're going to do is go today in the troposphere and talk more about infrared radiation, or what we would call heat energy or heat radiation. So the kind of the simple takeaway that I want you to get from all of this, when I look at my electromagnetic spectrum, I can see that their wavelength is increasing, that these values represent the wavelength in meters, and that when I go from UV to infrared radiation, we're just going to jump over that visible spectrum for a minute. When I move in this direction, I can see that the wavelength is increasing. Now remember, all we're talking about there is kind of the distance from one high part of the wave to the other, and that wavelength is related to the energy of a wave. So as I am moving across from ultraviolet to infrared radiation, I'm increasing the wavelength. I'm going from that amount of energy in a small little wave to that amount of energy kind of spread out over a bigger wave. Now we're not going to let the AP physics people check us on this. It's a very simplistic way of explaining to you that big idea that when I have UV versus infrared or heat radiation, it's a different amount of energy. So I think you get that kind of conceptually, that idea of why stratospheric ozone is important. The learning objective on the College Board says that stratospheric ozone layer is important for the evolution of life on Earth and the continued survival of life on Earth. That's a pretty profound statement. It really shows us the importance of the development of our atmosphere, what sets our planet apart from other planets in our solar system. And we're going to take that idea about global change and move forward with our discussion for today. So our lesson's pretty straightforward. We're going to dig into these three learning targets that all cascade in from one to another. What is the greenhouse effect? We're going to explain a process here. That's a very common learning target. And boy, I mean, something that we're probably going to see on an FRQ in one prompt or another, because we remember this is one that I often start off with. I'm going to kind of explain a process first and then start making deeper connections. We're going to look at that process of the greenhouse effect and relate that process to understanding a broader environmental issue. What happens when the concentration of greenhouse gases increases or gets outside this sort of normal range that our planet is used to? And then I'm going to extend that even further to look at global climate change and do some interpretation of results. So let's go ahead and get started. This is a really important unit, one that all APES teachers feel so passionate about teaching, and one that really filters down into every unit that we talk about in environmental science. So I'll mention it now and reiterate it later in our lesson, that many of the implications of global climate change we'll come back to during some of our review sessions when there's a really tight link between some human impact or on mining or agriculture or urbanization, and we'll always make sure while we're doing that to link it back to this lesson as well. So let's start off with the process of the greenhouse effect. I've got a little diagram here. This is my troposphere. That's the layer of the atmosphere closest to the Earth. Here's the sun. Here's a bunch of molecules that we can see. These are the five examples of the greenhouse gas molecules that our curriculum recognizes as being super important. Well, one of these you already know about, but you should recognize this from yesterday. This is a chlorofluorocarbon, a CFC. I've got a carbon, and in this case, 3 chlorine and 1 fluorine connected to that. So not only is that molecule in the stratosphere, it's a bad molecule because it breaks down that beneficial ozone, but in the troposphere, now that Dr. Sowell talked about that, in the troposphere, CFCs are greenhouse gas molecules, and you'll understand what they are in a minute. Dr. Sowell also talked about methane the other day. Remember that was in the landfill when all those layers of trash got compacted and pressed down, and there was anaerobic breakdown or decomposition of the organic waste, released methane. We all know about carbon dioxide as being a greenhouse gas. Water vapor is one that a lot of people may not be overly familiar with, so we're going to come back to that in just a couple of minutes. And then N2O, or nitrous oxide. I'm just going to identify it as a greenhouse gas right now. We're going to talk about sources and impacts of that in ways or solutions that could mitigate the amount of that in our unit when we review some agriculture practices. It'll make a lot more sense to understand how that's formed when we review some of those practices starting next week. So what the heck is going on here with this process? Well, the first thing that happens is energy comes in from the sun, and that energy strikes the surface of the earth, and a lot of it is absorbed. It warms the surface of the earth. If I walked outside and lay down on the pavement right now on a sunny day, I would feel all that energy because some of that energy is being absorbed and heating the surface of the earth. Another thing that can happen is when that energy strikes the surface of the earth, it can be reflected back out into space. Now, yesterday with Dr. Sewell, you reflected some of that even before it reached the surface of the earth. So once it reaches the surface of the earth, it's absorbed and heats the earth's surface, or is reflected back out into space. All of that energy that's reflected back out into space, it can be what we call re-irradiated. So here's this energy being reflected back out into space, and boom, it hits a molecule of a greenhouse gas. And I'm going to dig in deeper to the chemistry of those gases in just a second, but if it hits a molecule of a greenhouse gas, that energy is re-irradiated back down to space. And if that energy that's reflected back out into space, if it makes its way through the atmosphere without hitting a molecule of a greenhouse gas, then it is re-irradiated back out into space. So again, energy that from the sun can be absorbed by the Earth's surface and heat it. It can be reflected back out into space. Some of the energy that's reflected hits a molecule of a greenhouse gas and is re-irradiated downward, and some of it that is reflected out makes it all the way through the atmosphere. So you can think about, if I extended this image, you can think about molecules of greenhouse gases in the atmosphere like a thermal blanket that we put over the atmosphere that keeps our atmosphere warm. This idea of the greenhouse effect was first proposed in the 1850s. This isn't a new idea. It's the chemistry of it is actually pretty straightforward. It's pretty simple science. And in the 1850s, physicist John Tyndall, you may recognize him from the Tyndall effect, that refraction of light. He actually measured in the laboratory how much heat or infrared radiation different gases like CO2 absorb. Remember that the diagram of the electromagnetic spectrum we just looked at. This is UV light coming in. Once that strikes the surface of the ground and is re-irradiated back into space, it is infrared. You can just call it heat energy. And that's the connection I wanted you to be able to make. Because when we explain how these molecules trap or re-irradiate that heat back down to space, we have to understand a little bit about why it's able to pass right through the atmosphere on its way in, but it's a different wavelength, if it's a different form of energy on its way back out. So what's up with water vapor? Let's take a look at that first, because that's one of those greenhouse gases that a lot of times kids are like, I had no idea that was a greenhouse gas. I just think of water vapor in connection with the hydrologic cycle. So here's a statement about how water vapor functions, if you will, in our atmosphere. And I'm going to give you a minute to reflect on this and see if you can explain it. Water vapor does not control the Earth's temperature, but is instead controlled by the Earth's temperature. Understanding this really kind of gets at why we don't really talk about water vapor being a real big player in the greenhouse effect. So here's a little bit of a hint for you. How'd you do it? Let's see. Let's go through a process here and see if you can put in up or down arrows. So if I increase the temperature, because I see what we're looking at here is how water vapor is controlled by temperature. So if I increase the temperature, what happens to this arrow? Do I increase or decrease the rate of evaporation? Well, I increase it. I have more water going from the liquid to the gaseous phase with an increase in temperature. So if there's more water vapor in the atmosphere, what do I do to the amount of precipitation? I increase the rate of precipitation. So water cycles through the atmosphere so quickly, it doesn't stay in the atmosphere for days as water vapor. That water vapor builds up, it condenses, and it falls as precipitation. So a lot of times you'll hear climate scientists talk about water vapor as an amplifier. It kind of it amplifies the impact of those other greenhouse gases. Well, what about nitrogen and oxygen? Those aren't greenhouse gas molecules. They weren't one of the 5 molecules that I showed in this initial picture here in the atmosphere. Well, wait a minute. If I go back to the unit on the atmosphere, we learned that all of these gases together, every other gas in the atmosphere, all added together, other than nitrogen and oxygen, all together than 1% of all the gases in the atmosphere. So there's a very small concentration of them, yet boy, are they important for explaining life on our planet. So I just want to make sure you're clear on a little bit of an idea of how greenhouse gas molecules work. Because remember, that reflected radiation, if it hits a molecule of a greenhouse gas, I said it gets trapped and re-irradiated back out into space. But if it hits a molecule of N2 nitrogen gas or O2 oxygen gas, it passes right on through. So what's the difference? Well, I have these cute little animations that show you nitrogen. The nitrogen's a little longer, so I'll start it and kind of describe it as you're watching it. This is a molecule of diatomic nitrogen gas, triple bond holding those two atoms together. And if that gets hit by that outgoing infrared radiation, it hits the bonds of that, and there's a vibration that happens, but it's only going kind of in one direction. So there's just not that much energy exciting those bonds, then it just is able to go right through there. Well, let's look at what happens with CO2. CO2 is a linear molecule. I've got one carbon, each double bonded to an oxygen. And watch what happens when that gets hit, when the bonds of CO2 get hit with that whoa. So not only is let's play that one again. That's pretty cool. Not only is it vibrating this way, but I got vibrations going in other directions. So when infrared radiation hits the bonds of that CO2, it's got more, its energy has more ability to cause a vibration of those bonds. And that's what really is re-irradiating that heat back down to space. Now let's take a look at methane, because we're going to compare methane to CO2 a little bit later. Methane, simple hydrocarbon, carbon with 4 hydrogens bonded to it. So I got pull and I got vibration going in all kinds of different directions there. So that explains why some gases are able to trap that outgoing heat energy and keep it to warm the lower layers of our atmosphere. And it's a pretty amazing process when you think about it, because it's really what makes life on our planet habitable. So let's take a look at those different greenhouse gases and see if we can make sense of how one is different than from the other in terms of their ability to trap heat. And there's 2 big things that we look at. Number 1, their ability to absorb energy. And you now know that you don't have to be able to explain that, just so that you can recognize or identify that their ability to absorb energy has something to do with its bonding structure and those bonds vibrating and dissipating that heat. But the next thing is how long that's going to stay in the atmosphere. Its lifetime. How if I generate some CO2 from burning coal today, that CO2 could be in the atmosphere for up to 100 years. So we are leaving future generations our carbon dioxide that they're going to have to figure out how to deal with. So scientists want a way to measure and analyze the impact of different sources of greenhouse gases. And like I said, this is where when we do different reviews of human activities, we'll link back to specific greenhouse gases. So how is it that I compare the release of methane from a landfill to the release of carbon dioxide from burning coal? Well, scientists have developed this scale that kind of puts everything on an equal playing field, sort of an equal unit of measurement, if you will, and it's called the global warming potential. So we make carbon dioxide the baseline value. Carbon dioxide has a global warming potential of 1, and all the other greenhouse gases are ranked relative to that baseline of 1. So for example, CFCs, they have the highest global warming potential of any of the greenhouse gases. It sort of depends. The range of values is huge. It could be 5,000 years up to 10,000 years. Thousands of years that these CFC molecules are going to be in the troposphere trapping heat. Forget about the stratospheric for a minute. We're focusing on them as heat-trapping greenhouse gas molecules, and the reason they've got that high global warming potential is because of how long they last. They're very, very stable. Methane, on the other hand, still has a high global warming potential. Remember, CO2 is 1. Its global warming potential is 25. Not so much because of how long it lasts. Methane's going to cycle a lot. It's still a natural carbon compound. We just disrupted the rate at which it's moving through the carbon cycle, but there's still processes that will break that methane down much more quickly, obviously, than this man-made CFC molecule. But remember that methane with those 4 bonds had vibrations and going in all different directions, and that's why its greater heat trapping ability is what gives it so much higher of a global warming potential. So let's do a quick check for understanding and make sure some of that initial content makes sense to you. Here's a simple multiple choice question that we would have seen on a released exam. Which of the following greenhouse gases does not contribute contributes significantly to global climate change because it has a short residence time in the atmosphere. So this should have been pretty easy. Obviously, water vapor. And remember that you're not going to have multiple choice on our national exam, but Dr. Sowell and the College Board and all of your amazing APES teachers and I feel really strongly about the idea that you need some pretty good understanding of how our climate system works, because you not only are going to be an amazing scientist, but you're going to be a citizen that has to live in a world that is going to have carbon dioxide concentrations in the future that you again are going to have to manage. So it's important you understand the difference between the impact of different greenhouse gases. Here's another one. 65% of global greenhouse gas emissions are made up of carbon dioxide, while 16% are methane. So there's a pretty big difference there. Which of the following best explains why scientists are increasingly concerned about the effect of methane emissions, even though they represent a relatively small percent of overall emissions? And obviously the correct answer here is to do with methane's global warming potential. Remember, methane is not a synthetic organic compound. It's a naturally occurring compound emitted during anaerobic decomposition. Cows fart it out, cows belch it out. This has the average residence time isn't really the correct answer. Remember, that's not the reason that methane has a greater impact. It's because of its heat trapping ability. And this statement just doesn't really make much sense. And it's nothing to do with the production of photochemical smog. So great job on that one. And again, really focus on this idea that we're still kind of exemplifying how to do a good explain why, which is a skill that we're going to need to have. Let's go to the next section that we're going to talk about, and why the heck is the greenhouse gas or the greenhouse effect important. I think intuitively you get this statement that it results, the greenhouse effect results in a surface temperature necessary for life on our Earth. We like to sort of talk about our planet Earth using an analogy of Goldilocks and the Three Little Bears. There were some porridge that was too hot, some that was too cold, and baby bears was just right. Well, our planet's kind of like that too. Some planets are way too hot, like Venus, because it's a lot of CO2 in its atmosphere to a large extent. Some are way too cold, like Mars, and then there's Earth that has just the right atmosphere. And a lot of that has to do with the amount of CO2 in our atmosphere. So let's kind of break down this model a little bit that is showing me two different lines. One is carbon dioxide concentration in parts per million. The other is this temperature difference in degrees Celsius. I'm going to come back to the scale in just a minute. So don't worry about this for a second. I really kind of want to focus on the interpret part of the diagram for now. So I can see that the concentration of CO2 in the atmosphere and average global temperature throughout Earth's geologic history are strongly correlated. Look at my x-axis here. This says years before the present. So on the very left-hand side, 800,000 years ago, and then this would be today. Much of this data comes from examining ice cores, little gas bubbles in the ice cores that they can in glacial ice from both Arctic areas as well as high altitude mountain areas in South America. People that study the cryosphere, the part of our planet covered with ice, go to glaciers all over the world and collect these core samples that they then analyze. So what else can I kind of interpret from this? Well, it seems like there's a cyclic pattern to the data. It seems like there's a correlation and that both the temperature and the CO2 go up and go down. However, I'll point out to you that throughout most of Earth's geologic history, there's an up and a down value, a high and a low value, but they seem to sort of stay within parameters, within an upper limit range and a lower limit range. And sometimes the rate of that change, like it looks like it goes up rather abruptly, but then it seems to come back down to about an equal amount that it went up. So there are these oscillations, but over a really long period of time. Think about if you were to make a graph on a piece of graph paper and you had to calibrate it so that you could represent 800,000 years. So what looks like initially is a really drastic overnight abrupt kind of change. In fact, it's actually happening over tens of thousands of years because I've got such a big span of data. So the greenhouse effect is the natural process where just the right amount of greenhouse gas molecules in the atmosphere trap just the right amount of heat. And it's important because it maintains temperatures on our planet within a habitable range. There's upper limits and lower levels, but I stay within these range of values. So I want to make sure that you're clear. I made the statement that we have just the right amount of greenhouse gas molecules, and the concentration of carbon dioxide has changed throughout Earth's geologic history, but it stays within a range of values that are just the right upper and lower range of values because that's what our planet has evolved to be used to. And we're going to dig into these cycles a little bit more. This graph of this geologic history of climate, of CO2 and temperature, is what we call paleoclimate, ancient climate. Well, let's see if we can move on to that next learning target then. Can we take our understanding of this process of the greenhouse effect and use it to explain a broader environmental concept? Why is it that greenhouse gases are increasing, and what is the impact of increased concentration of greenhouse gases? So I want to zoom in on that little yellow bracketed part of the graph, same graph that we just looked at. And whoa, now I have to take back that statement I just made that we always seem to stay within this upper and lower limit. This part of the graph in the most recent years doesn't look like it's anywhere near where I have had upper limits throughout 800,000 years of climate data that we've been able to record. And it's this really steep upward part of the curve over a little tiny short period of time that's got us concerned. We're going to come back in a little bit to the rate of that change. How are we doing so far? Great. I wish I could see you all and get some feedback. Okay, so let's look at the essential knowledge statement that has to do with that idea of increased concentration of greenhouse gases. Excess amounts of greenhouse gases cause environmental problems, and there's all kinds of environmental problems that link back to climate change. So like I said, I don't want to dilute any of those because it's really important that you get all of the different ways that increased concentration of greenhouse gases is impacting life as we know it on planet Earth. And so we're going to sprinkle those impacts throughout the rest of our review session. We'll certainly go into some of them today, but we'll try to address some of them in context to what's causing specific human impact is causing that increase in concentration. One of the things we can point out right away, because we looked at it just the other day when we looked at Zika virus, for example, is that we know that the range of tolerance of disease vectors is spreading as climate zones are being pushed. Habitable climate zones are changing as a result of that. Other big things that you probably hear about that maybe don't really know much about are melting ice sheets and rising sea levels. So let's dig into that a little bit. There are kind of two big causes for sea level rise, and the number one most important factor is what we call thermal expansion. So let's kind of go through this increase-decrease process again. This is a really helpful strategy on your FRQ when you have to describe a process. It oftentimes isn't enough to simply say increased concentration of greenhouse gases causes a change in temperature. I've got to be specific as to the direction of that change or the direction of that swing. So I like to prompt students to, as you're taking notes and processing your FRQ prompt, it's sometimes good in your head and then transferring that to paper just with up and down arrows to say this is what happens and here's how the system responds to that in the specific way it responds, not just a blanket generic statement that it changes in some way. So we know that temperatures in the atmosphere are increasing. Even a diehard climate science denialist can't deny the data that global temperatures are increasing. Well, we also know that increasing the temperature of the atmosphere increases my sea surface temperature. There's a lot going on in deep ocean as well, but we're just going to focus on sea surface temperature. And how do I know that? I'm not just making this inference. NASA has given us an amazing amount of data from these Argo floats that they disperse like thousands, 3,000 of them, I think, throughout all of the world's oceans. And it's a remote sensing device that is constantly sending data back to satellites for them to track everything from temperature to carbon dioxide concentration, salinity. We're getting just vast amounts of information. So we can track changes in sea surface temperature as well. Well, if I increase the temperature of water, I get what we call thermal expansion. It's this basic kinetic molecular theory that when I heat up those molecules of water and they get more kinetic energy, they expand and take up room. And that you're like, okay, that can't be that much. Well, think about all of our planet that's covered with water and all of that water expanding just a little bit. In fact, overall, the current rate of sea level rise is 3.3 millimeters per year, and a large amount of that is directly related to thermal expansion. So here's some of that satellite data that NASA has been collecting for us. Sea height variation in millimeters, and again, that trend line is just really straightforward, up and up and up since we've been collecting that data. The other big cause of sea level rise, and the one that you probably would maybe go to first, that you're maybe a little more familiar with, but remember the number one cause of that sea level rise per year is due to thermal expansion. The next major cause is melting of ice, but not all ice on our planet is created equal. We have land ice and we have sea ice. So land ice is glaciers, and you could think of it a little analogy here of a glass of water. So if I have a glass of water and I drop an ice cube into it, that's my glacier ice that as it warms, maybe it even becomes liquid water and falls into the ocean basin. Sometimes warming that glacier creates little water to seep down in little crevices, and it kind of lubricates it, so we get shearing or calving of big chunks of ice. You'll see a little image of that in a minute. But when I drop that ice into my glass of water, that ice cube displaces that volume of water and it raises the level of water. If I have sea ice, if I have an iceberg out in the middle of the water, that ice cube was already in the ocean and had already displaced that water, so when it melts, it's not altering the overall volume of water. So if you need to talk about rising sea levels or understanding the difference or communicating to other people the impact of increased temperatures, it's the idea that increased temperatures cause thermal expansion and the melting of land ice, both of which contribute to a rise in sea level. Let's do a quick check on that big idea, and then we'll keep going with climate change. Oh, here's a beautiful graph that is showing me how much sea ice has decreased from 1980 to 2005. Even though this is a multiple choice question, it could be an FRQ calculation as well. So this looks like the graph that I just showed you. Now what we're going to do is do a calculation with it. Notice the up and down trend. We're going to come back to that in a minute, and I've got a nice trend line on here. So I'll give you a second to take a look and see if you can do that calculation. So this is a percent change problem, and I have to look at my starting value, my ending value, and then remember I divide that by my starting value. So it's how much that changed relative to what the starting value was. And you should have come up, you may have been a little bit off on your reading of that exact data point, but you certainly should have come up with something pretty close to 30%. So this is actual data, and that's a pretty dramatic loss of sea ice from 1980 to 2005. All right, let's go on to the next topic that is going to add to our understanding of the greenhouse effect, increasing concentration of greenhouse gases, and global climate change. And it's the really big idea of feedback loops. When we talk about positive feedback loops, initially students want to think, oh, it's a good thing because it's positive. But the term positive feedback loop means that we are inputting something into our system that is accelerating the rate of that process. And what we're looking at here is our climate system, our atmosphere, and the input is increasing concentration of greenhouse gases. So we understand at a core level how greenhouse gases work and trap heat. Now we want to look at how increasing concentration of greenhouse gases actually puts into motion a chain reaction that amplifies those impacts. And it's happening most significantly in Arctic regions. So I have a cool little animation from NASA that I'll have you take a look at. Focus on that solar radiation that's being absorbed and that solar radiation that's being reflected back out into space. There's just some nice NASA music there. We don't need to hear that. This is that shearing at the base of the glacier. We call it calving, where the edge margin of that glacier falls into the ocean. That calving is a natural process, but it's accelerating. So that was pretty cool, wasn't it? Let's just kind of make sure we're all on the same page as to what we saw happening there. So we can see the northern pole of our planet that is covered with, it's white, it's covered with snow. And we say that that surface has a high albedo. Remember that solar energy is either absorbed or reflected. So when that incoming infrared or heat radiation hits the surface of white-colored snow surface, most of it is reflected back out into space. That's why I wear light white-colored clothing in the summer to keep myself cold, because a black shirt's going to absorb a lot of heat. We say that that light white-colored snow surface has a high albedo, a high reflectivity. Once that snow melts, and it is now liquid water. That liquid water is very dark. Liquid water, dark ocean water, and other terrestrial land covers, whether it's an urban area or forested area or agricultural land, they all have different albedos, but they all have lower albedos than that really white one. So this dark colored ocean water may have a very low albedo, as low as 10%, meaning only 10% of that energy is reflected, the rest of it is absorbed. So let's put this in to play by looking for some patterns and see if we can make a connection and define what we mean by that positive feedback loop. What happens when I warm the atmosphere and the snow melts and I change the albedo? So you see a really nice graphic superimposed over this melting, and we'll look at the graphical stay there at the end so we can make sense of the graph in a minute. What I want you to notice is this sort of waxing and waning of the amount of sea ice. And that's a natural process because in the Arctic winter, a little bit of ice builds up, and then in the Arctic summer, it kind of thaws and shrinks back a little bit. But again, we see that our Earth is in a balance, that these values are typically maintained within a range of values. And by sea ice minimum, measured in millions of square miles over time, I think I got about from 1980 to 2013-ish there, I can see that over time, if I put a trend line in there, I'm decreasing the minimum Arctic sea ice. By minimum value, we mean that summer value when it's at its lowest, area of accumulation, if you will. So each year, the data point that's measured there is when it's at its lowest point. And so even though I've got this pattern of building up and falling back and building up and falling back, except each year it's not building up as much. It's falling back more and more and more and more, so that Arctic minimum of sea ice is drastically decreasing. Well, oh, that's the same thing. Now let's see if we can connect that kind of all together with sea level rise. So here's this graph of temperature and CO2 concentration that we looked at early on. Now we put sea level rise in there as well. And boy, it's just like a mirror image again as well, right? I had to take each of those graphs and superimpose them over the other, and there's a relationship, a strong correlation that we can explain because of our knowledge of environmental science. So we know that temperature and CO2 have changed throughout Earth's paleoclimate, throughout Earth's geologic history, and these have led to different periods of different climates throughout these past 800,000 years. When I have a really cold period, what we call an ice age, what geologists would call a glacial period, when there's a lot of ice on our planet, and then I have these really warm periods where I'm in an interglacial period and there's very little ice on our planet. And this is a normal process that these variables have waxed and waned over time. But the thing we have to come back to and keep in mind is that we are measuring these changes across 800,000 years. And although sea level rises, sea levels have risen when it's warm and fallen back when it's cold, they have always stayed within a range of values. And even though initially that change may appear very stark and dramatic, this is still measured over this right here is 100,000 years. So this change is still measured over tens of thousands of years. It is a slow process, and our planet works in sync to adjust to all of these changes. Hey, let's take a look at a couple of more, I've got two more feedbacks to look at, and then we'll come back and make sure you're clear on that concept of what a positive feedback loop is. So melting permafrost is another example of a positive feedback loop where a forcing or an input to my system causes a chain of events that accelerates that process. So as atmospheric temperatures warm, this permafrost, this area of below the initial layer of vegetation, this area that is permanently frozen. And throughout certainly thousands of years of human recorded history, and we can go back and look at where indigenous populations have lived for the past couple thousands of years, this has been permanently frozen land across much of the northern latitude tundra on our planet. When I warm the atmosphere, this permafrost melts, and that melting permafrost, think of this as the bottom of that landfill Dr. Sowell talked about, all of that organic matter that's been building up, it warms up a little bit, and those microbes underneath there just come to life, and they start breaking down that organic matter. And what do? They release all that carbon as methane. We're going to readdress that big concept when we look at the carbon cycle end of next week or the week after, but this is a really startling number. 1.5 trillion metric tons of carbon are stored in permafrost, and this has got climate scientists really scared as we try to create climate models where we put in all these different variables that are going to impact the concentration of greenhouse gases and thus the temperature and thus life as we know it on our planet. Remember, methane has a global warming potential of 25. Doesn't stay in the atmosphere as long, but it traps a lot of heat because of those vibrating bonds. If we start releasing all of this carbon as gaseous methane into the atmosphere, we create this positive feedback loop where I increase the temperature, I melt the permafrost, releases mostly methane, which traps more heat, which causes more warming, which causes more thawing, which releases more methane. It's not a good thing. It's a bad thing, but it's a positive loop because it's amplifying or accelerating that process. Something Dr. Sowell is going to talk about tomorrow is this idea of oceans releasing carbon dioxide. Remember the nifty process of using these up and down arrows to make sure I can explain this process correctly. I increase the temperature of the atmosphere, I increase sea surface temperature, and that means that I decrease the amount of dissolved oxygen gas that water can hold, which means that that gas has to go somewhere. It goes from being stored in the ocean water into atmospheric CO2. Now it's a greenhouse gas in the atmosphere that causes more warming, which releases more CO2 from the ocean, and it amplifies that. You've been hearing a lot about models if you have been listening to any of the news about the coronavirus and projections as to when we're going to reach our peak outbreaks. And the models that those public health officials use take into account all of the different variables that could impact that peak. How much social distancing are we practicing? What kind of data do we have on how many people are testing positive? Because we know that represents exponential growth. Well, climate scientists use similar kinds of ideas for making models, and their models have been super accurate throughout history. We can judge good science by the ability to make predictions, and then 30, 40, 50 years later, those things happen. That's exactly what we've seen happen with climate science, is that many of the predictions that were made in the 1970s with some of the first papers that were written about climate science, those things are coming true with quite a large degree of accuracy. Like any model, we're going to have an upper and a lower range of values. How much warming do we see? How much are sea levels going to rise? And the tricky thing about those models, and why we believe that anything the models may have underestimated, is because we are starting to understand the huge impact of these positive feedbacks, these forcings that are amplifying what started from a paleoclimate standpoint. What initiated that forcing to cause an increase in temperature and release of methane from permafrost and release of CO2 from the oceans? That was a kind of a small forcing to start with, but then once we just released a little bit of CO2 or from the ocean or released a little bit of methane, they just amplified that process and caused more and more and more warming until the sun moved a little bit further away from the sun and we went back to a cold period. Part of a natural cycle, but remember, it's the rate or the period of time over which these drastic changes are happening. So here's just kind of a quick NASA summary of some of globally the events we see. It's hard to tell. This is a little thermometer symbol. And I will point out that there are some areas in North America that may actually cool. We have wonky things going on with our climate in Wisconsin, really drastic changes in severe rain events, and we'll talk about that in another unit because of all that water vapor in the atmosphere and that latent heat energy. But almost all places on our planet are experiencing negative consequences of increased concentration of greenhouse gases. And again, we're going to dig into some more of those specific impacts in a unit when it'll link together and make a little more sense. So let's do a quick check for understanding on that idea of positive feedback loops with another multiple choice question. Give you a second to look at this one. Which of the following best explains the impact of climate change on polar regions? And you should obviously have picked out letter D. Can you see letter C? Here's a really good example of why I want to use those kind of up and down arrows, because it's super easy to get the part of that chain of events going the wrong way, increase versus decrease, and be prevented from earning a point. Here's one more on kind of the up and down process. This event leads to this event to describe that process. So see if you can connect these events that show a positive feedback loop in an Arctic ecosystem. And again, see all those increase decreases? You should have picked not that answer. I'm sorry, the correct answer should be D. The temperature Global temperature increases, permafrost decreases, methane increases. I'm sorry, I circled the wrong one there. The correct answer should be letter B. Global temperatures increase, permafrost decreases, methane increases, and global temperatures increase. Oops. So let's wrap up with looking at one last piece of content to kind of bring this all together for us, and looking at current trends in carbon dioxide. This is what we call a Keeling curve. It was named after Dr. Keeling, who started collecting daily carbon dioxide concentration records at the Mauna Loa Observatory in Hawaii. And this has been kind of this a very long record of carbon dioxide concentration in our atmosphere. I believe his first reading was taken in 1958. And there's a couple things that we notice here. Obviously, overall, the trend line is an increase in CO2, just like that kind of waxing and waning of sea ice. I see a lot of up and down of CO2. We're going to explain that next week when we look at the carbon cycle and photosynthesis. But what I really want to drive home here to you is I keep talking about that idea of paleoclimate being measured across 800,000 years. And what look like really abrupt changes actually are occurring over a span of a pretty long period of time. Well, if I look at the rate of change, and if I just do the slope of the line, like if I look at from this early decade, 1960 to 1970, and I looked at the change in Y, the change of values on my Y-axis, I went from about 324 to about 314, which is where I started out in 1960. Over a span of 10 years, that comes out to a rate of change of 1 part per million per year. Now let's look at what's going on from 2010 to 2020. Here are my Y-axis values for 2020 and 2010. I had a change of 30 parts per million over a span of 10 years. That's 3 parts per million per year. This is just really good evidence to support climate science, because not only is CO2 increasing, but the rate of increase is accelerated. I love that graph. We'll look at that again in our carbon cycle activity. Let's wrap up our discussion today by looking at an AP exam practice question. So we make sure we look at that last practice or skill that we wanted to address. The graph below shows us temperature anomalies. So it's really important that you understand that idea of a temperature anomaly and changes in the temperature anomalies in the Arctic from 1900 to 2016. And the first question is, describe the difference in the change in temperatures in the Arctic with the global change in temperature over that same period of time. And next, support the following hypothesis. The change in temperature relative to global temperature can be explained by the change in albedo. I'll give you a little bit of time to think about those. So there's a couple different ways I could describe that difference. I could say the temperature in the Arctic during that time period went faster than the global temperature, that the temperature in the Arctic over that time period was increasing at a greater rate, more degrees per year. And then being able to explain or support this hypothesis by trying in that explanation of a positive feedback loop. The Arctic is being impacted at a greater rate than the rest of the planet because of that drastic change in albedo. Now, really, we are certainly changing the albedo of other land surfaces, but nothing that went from that dramatic, a change in the amount of energy that's being absorbed. So as that light-colored snow surface melts, more energy is absorbed, which causes more warming, which causes more melting, which causes more warming, accelerating or amplifying the impact. So hopefully you learned quite a bit about the basics of the greenhouse effect and climate change. I think you can explain those processes that are important in understanding the greenhouse effect. We can now relate that to why increasing concentration of greenhouse gases can ultimately lead to climate change. We're going to continue with this exciting Unit 9 on global change tomorrow. Dr. Sowell will wrap up the week by coming back to this idea of CO2 in the oceans and looking at ocean acidification. Have a fabulous rest of your day. Stay safe.
Hello, APES. Welcome back to our online lessons for AP Environmental Science. So my name is Dr. Sowell, and I teach APES down here in Jacksonville, Florida. So before we jump into today's work with ocean warming and ocean acidification, I do want to point out some new updates that we just found out about the upcoming AP exam. Now, your AP teachers will have a lot more information, and you'll probably see some more information and details posted on the College Board website. Excuse me. But I just want to go over a few things that we do know at this point. So you know at this point that you'll be taking it at home, but the date of the exam is Monday, May 18th at 4 o'clock Eastern time. It's going to cover units 1 through 7, so as laid out in the course exam description. No multiple choice, we do that already, and there's no math. So let me back up a little bit. You do not need a calculator. So you may see some quantitative data in graphs or charts or other means, but you won't actually have to do any calculations yourself. You may need to look at that data and make some inferences or explanations based on that data, but you won't have to do any mathematical calculations per se. Then we've got 2 FRQs that we know is going to be on the exam. The first one is going to mimic the way the first FRQ was described in the course exam description booklet. It's the design and investigation FRQ. So there's going to be some type of experimental design aspect to part of that question. It will be asking you other things, and you'll have to do other skills in that first question, but it is all framed around a scientific investigation. And that's 25 minutes to do the question and 5 minutes to upload your response. At 5 minutes to upload your response, you will get more detail on what that really means a little bit later on. But to answer the question, it's 25 minutes. FRQ number 2, that's 15 minutes, and this is called the Analyze an Environmental Problem and Propose a Solution FRQ. So both of these FRQs, number 1 and number 2, focus on some specific skills. So Ms. Sasser and I have been talking about these practices and skills over and over and over again. Well, now that we know which FRQs are being tested, we're going to narrow our focus to some of the specific skills associated with those 2 FRQs. It's not going to be a big difference than what we've been doing so far. We're just going to get a little bit more myopic and focused on which ones you talk about. So that is an update on the exam. Again, check with your instructor, check the College Board website for more details, and I'll share more as we go along. So let's just kind of warm up our brains here. So Ms. Fassler did an insanely good job the other day talking to us about greenhouse gases and climate change, and she talked about the idea of more heat being trapped into our atmosphere. I want to see if you can translate that information over into thinking about the oceans now. So this question says, which of the following best describes the primary cause of global ocean warming? So take 30 seconds or so and choose the correct answer. All right, so hopefully you picked D, an increased global temperature from an increase in greenhouse gases in the atmosphere. And this goes right back to Ms. Fassler's conversation the other day. In fact, I just grabbed a screenshot of her lecture as I was listening to it. She did a really fantastic job talking about these greenhouse gases, carbon dioxide, nitrous oxide, methane, CFCs, and water vapor, and how these 5 gases re-radiate heat back down into our Earth's atmosphere. So while certain wavelengths of energy can pass right through, this heat energy, this different kind of wavelength is bounced back and creates a more warm planet and the resulting climate change. So here's what we're going to do today. Here's our goal. So our 2 content goals are number 1, to discuss ocean warming, and number 2, to discuss the issue of ocean acidification. These are very 2 unique systemic changes to our oceans that have some very specific and measurable changes that we'll talk about today. While doing so, we're going to look at these 2 practices: concept explanation. Can you articulate an understanding of an environmental concept in written form and make it sound like you've taken the course, not just memorize some facts? And second of all is the practice of scientific experiments. Can you design your own experiment to perhaps investigate an environmental issue, or can you interpret somebody else's experiment and pick apart some of the unique things they did in their experiment process, their methods? So just before we start, I always like to start by kind of thinking about how this ties into some other units. And so some things that I thought about today was clearly aquatic biomes. We're looking at the ocean. And this comes from Unit 1, Topic 3, carbon cycle. You obviously saw this with Ms. Fassler yesterday, and we'll continue to involve the carbon cycle in particular here with our 2 topics. And then also, again, that notion of ecological tolerance. That's popped up in 2 or 3 times so far because it is such a great tool to explain the effects on species of different environmental issues. So here's what we need to know for this first stop, 9.6. By the end of this section, you should be able to explain the causes and and the effects of ocean warming. So to get there, we're going to do two things. We're going to describe why those greenhouse gases are causing ocean warming, and then we'll look at some very specific effects of ocean warming on marine species. So Ms. Bassler mentioned the other day that this very historic record, 800,000 years ago, paleoclimate, and we can see upswings and downswings with carbon historically through time. But then we have this era in our modern times, from 1950 beyond, really, where we see this big spike in carbon dioxide levels. And Ms. Bassler also showed you the Keeling curve. So this is our modern standard of record keeping for the carbon dioxide concentrations over Hawaii. And so we can see the concentrations of carbon dioxide, the ppm part per million, increasing over time. And Ms. Bassler also pointed out uniquely that the rate of change is different. She looked at the slope of the line. So back here in the 60s, it was averaging about 1 part per million per year. So it was going 1 part per million per year up. Now in more modern decades, we're looking at almost 10 part per million, or I'm sorry, 3 part per million per year. So the rate has gotten higher. And again, the result of that is this enhanced greenhouse effect, global warming, and climate change. So the next logical step to take if we're talking about oceans is a warmer atmosphere is going to result in a warmer ocean. Why? More greenhouse gases are going to trap that heat within the atmosphere, and because 70%, over 70% of our Earth is covered in oceans, a lot of that heat is simply going to be absorbed by the oceans. Atmosphere heat transferred into ocean heat. And here clearly is one of our pieces of content knowledge from the curriculum guide. Ocean warming is caused by the increase in greenhouse gases in the atmosphere. So changes in the atmosphere causing changes in the ocean. So in particular, we're going to take a look now at sea surface temperature. This is the temperature of the ocean in the upper few meters of water. And if we just look at the anomalies from January and December from 1880 all the way up to 2020, you can clearly see there's much more of a positive anomaly, some increases in temperature in more recent times, and the overall trend is increasing. So why do we care? I think Ms. Bassler did a great job the other day of talking about why we care if the atmosphere is hotter, if the planet is hotter. Now we're going to drill down and go, well, who cares if the ocean is a little bit warmer? Well, it has some very clear effects. Ocean warming can affect marine species in a variety of ways, including loss of habitat and metabolic and reproductive changes. So again, going back to that range of tolerance that we talked about before, let's pretend I'm one of these little soldier fish right here, and I'm existing in my optimal temperature. I'm swimming around doing my thing, being a good little soldier fish, and I can survive, I can grow, I can reproduce. I'm thriving in this optimal abiotic condition of temperature. But if it gets a little too cold or a little too warm, I may be able to survive and grow, okay, but maybe I'm not reproducing as well. Maybe my spawning activities have been altered, or breeding cues have been altered because of temperature. And then if we go even further on the left or the right, maybe I'm just hanging in there. I'm not really thriving or reproducing or growing, I'm just barely hanging in there. And if I go beyond my range of tolerance, I can't exist there. Now if I'm a fish and there's habitat elsewhere, perhaps I can move to avoid those extremes or those temperature anomalies outside of my range of tolerance. But if I'm something that is in a fixed position, let's say a coral, I'm going to have to stay there and either weather it out or not make it. So I'm going to show you some images without a lot of labels on them, just to see if we can find a pattern in these images. So I'm going to start with this. This is from 1967 on the northeastern coast of the North Atlantic Ocean, and you'll see some clear spots and some purple heavy concentration spots. And if we compare that with 1967 to 1990, we see that this purple stuff, whatever it's measuring, is going from being kind of evenly distributed along this range to being a little bit more concentrated up here and hardly anything down here. And then if we jump to 2014, we see the vast majority of this purple stuff in the north. Well, what this is measuring is the number of lobsters caught by lobster fishermen. So warming ocean temperatures is pushing the lobster population north. So the temperatures down here in 2014 is outside of the optimal range of tolerance for temperature for these lobsters, and they're moving north to colder waters. So again, this is not just about fish moving to other locations. This has some very real consequences. So it can affect metabolic rates. It might be altering when certain species reproduce. Sometimes those cues for spawning are temperature related. Habitat loss, we'll talk a lot about that today in terms of coral reef, but also temperature can affect the sex of an offspring. Sea turtles, for example, their determination of male or females can sometimes be affected by temperature. But what we're going to focus a lot of our attention on today is coral reefs. Coral reefs are being dramatically impacted by both of the things we're talking about today, warming oceans and acidic oceans. And so we'll first talk about how warming oceans affect them. So when we look at this coral reef, just take a second and stare at it, and you'll see, I mean, it's beautiful. We have lots of different coral colors. We see some fish, so the biodiversity seems pretty high, but you'll also notice this is pretty shallow water, low turbidity, and that typically means that the organisms there are going to require some sunlight, and that's going to become important in a minute. So coral reefs are important for a lot of reasons, and they are a good place to kind of practice some of the ideas that we mentioned earlier in the course. So concepts of biodiversity or species richness, and then just the dynamics of a food web and all of those trophic levels and energy transfers within this complex community. NPP, the primary productivity, would come into play here, and also symbiosis. And the symbiosis is a concept we'll look at next. So this is what a coral looks like. So a coral polyp is an individual, tiny, soft-bodied polyp, and it's got these little tentacles on the top, and these tentacles will grab plankton and eat up. But that only composes a small amount of their energy needs and food needs. The majority of their food comes from this photosynthetic algae that is living as a symbiotic relationship inside the tissues of the polyp. So it would be as if I had algae in my skin, and I could walk outside and get in the sunlight and feel full. It would be feeding me. So the algae has a great place to live, and the coral gets some of the nutrients from the photosynthesis of the algae. So it's a great symbiotic relationship, and they cannot live optimally without each other. So I do want to point out two other things. If you'll notice here at the bottom, it says a skeleton. So if you think about a coral reef, they're kind of these large mounds or hills of coral. Well, actually, the only thing that's alive on that are the top layers of coral. That's these living polyps with their symbiotic algae. Underneath that is the calcium carbonate skeleton that they have excreted. So this little polyp excretes this calcium carbonate shell to hold it in place. And then the next generation will cover that. And then the next generation will cover that. So that the outside is this living layer of polyps with the calcium carbonate skeleton underneath. All right, so how does this happen? So we've got dissolved CO2 in the water. We talked the other day about DO, dissolved oxygen. Well, there's dissolved carbon dioxide as well, obviously. There's photosynthesis and full food webs going on underneath the water, and carbon is a part of that, so CO2 is going to be dissolved in the water. Well, what these organisms do, they take that carbon in the form of carbonate, so carbonate ions, combine that with calcium to make calcium carbonate. That's where the shells come from. So you can see here as a picture of a bivalve, and their shells are made out of calcium carbonate. Over time, with pressure and heat, this could form into some sedimentary rock like limestone. This is a really big carbon sink. A lot of the carbon is stored long-term in something like limestone rock. So unfortunately, we have a phenomenon called coral bleaching that is becoming quite common and disastrous for coral reefs. So if you'll notice this picture on the left, high biodiversity, very colorful, we see other organisms, looks like a pretty healthy coral reef. We look at this right side, we see bleached coral. It's all white, but the color is gone. But in addition to the color, the other species have gone as well. The biodiversity radically goes down. So our goal now is to figure out why. What's going on here? So I'm going to show you a video clip now, and I really want you to, as you're watching this, determine two things. What are the causes of this bleaching event, and then the effects of the bleaching.
Corals are small animals, but they build structures that you can actually see from space. As we zoom in, we see the reefs where I work, a little island called Ofu in American Samoa. The ridge there, the edge, is the coral reef. And as we zoom in, we see what those reefs are. And the reefs are made of individual coral colonies, like we see now. That coral, then, is actually made out of a whole series of small polyps, they're called. This is a colonial organism, and the polyps themselves have all the structures that an animal needs. It has a mouth, it has tentacles, it has gonads, it can live, it can reproduce, it can grow. They're in a colony of genetically identical polyps. Now, the color on these tentacles, like I said, is not the color of the coral itself, it's the color of the symbiont. And as the focus racks in and out a little bit here, then what we see is that we can just see the little globules of the symbiont. Well, let's take a closer look. We'll go into a tentacle and see those. These cells, the symbionts, are not just floating around, they're actually inside the coral cells. Corals are simple, they just have two cell layers, an epidermis and a gastrodermis inside. The symbionts are inside the gastrodermis, and you can see it there. Now, this is a life form called a dinoflagellate.
So that dinoflagellate, that is the algae. So this is the algae living within the cells of the coral polyp.
It has chloroplasts because it's photosynthetic, but it has very odd shaped chloroplasts, like these yellow structures here. We're going to zoom into the chloroplast itself because that's where the damage happens during bleaching. What chloroplasts have in them, they have membranes called thylakoid membranes. Those membranes hold the proteins called the photosystems that then capture light energy and turn it into chemical energy. It's the molecules that turn all of the sunlight that we get on the planet into the food that we eat. The rain of photons down here hits these photosystems and they gather them up. Now, if the temperature goes up and if the light goes up, then they freak out. There's too much energy, the photosystems break, and they no longer can function the way they do. The rain of photon keeps going. The energy is still there, and as a consequence, that energy is now turned into reactive oxygen molecules. Those are damaging the cell, so it damages the inside of the symbiont, it damages the inside of the coral cell, and they spit the symbiont out. That spitting of the symbiont out by one coral cell is bad, but if the entire colony does it, then that's coral bleaching, which you can see here is simulated of the spitting out of these symbionts and the gradual whitening of this particular part of this particular coral colony. Well, when that happens across an entire colony, then the coral turns from its normal tan color into a white color. What difference does that make? The symbiont provides 75 to 80% of the energy the coral needs to survive. Without that energy, it can't make a skeleton and it can't live very long. So as a consequence, a lot of the corals that bleach eventually die.
So we just heard there's 75 to 80% of the energy that coral reef uses on a moment-to-moment basis is coming from that symbiotic algae living within their tissues. And if coral bleaching is happening from temperatures, it's a bad situation for the coral reef. So the content standard says ocean warming is caused by coral bleaching, or ocean warming is causing coral bleaching, which occurs when the loss of algae within corals causes the corals to bleach white. Some recover and some die. So here we get to a really interesting part of this story is, are all corals at risk? I mean, is this happening everywhere to all corals, the same degree, the same way? So what we're going to do now is explore a data set to look at that. Now, although this unit will not be tested on the AP exam, this type of scenario is fair game. So we're looking at a situation, we're looking at an environmental problem, and now we're going to step back and look at some data to help us understand it a little bit better. So that skill of interpreting visual representations or data sets is a skill that may be applied to the FRQs that you have to do on the exam. So again, our question now is, to what degree is this happening? Is it bad all over? And how can some recover and some not? So we're going to go to Egypt. So there is a great coral reef in the Red Sea off the coast of Egypt in Hurghada, Egypt. And we're going to look at the sea surface temperatures there in the Red Sea, because if we know coral bleaching is associated with temperature, we should be looking at temperature changes in the ocean as part of our data set. So this is a graph from Hurghada, Egypt from 2001 to 2002. And you can see here that the maximum monthly mean temperature is 29.8 degrees Celsius. That means the average hottest temperature in this location is 28.9 degrees Celsius. So if that's the average hot temperature, if I'm a coral reef living down here, all is good, all is good, all is good. This is going to be some heat stress here. This is where I'm going to be at risk of bleaching. So we see it happen here during July and August of 2001, and in the fall and the winter and the spring it goes back down, and in the summer peaks up again a little bit here and then goes back down. So scientists are really interested in these two moments because this is where the heat stress is going to happen and potentially bleach the coral. So we can zoom in on those two data points and kind of blow them up a little bit to take a little deeper look at them. So if we compare what's going on in 2001 to 2002, we can see that 2001 looks like it lasts a little longer. The x-axis are weeks, so this is lasting a little bit over a month, about a month, and the highest change in temperature is a good complete degree from 28.9 to 29.9. So during this time, this coral reef in Hurghada, Egypt experienced a month-long warming event, and it was pretty high, almost a full degree at times. The following year, it's a little less longer in duration, and usually only about half a degree. So why does that matter? In this situation on the right, it was probably about a bleaching possible. So this was a possible bleaching. However, this lasted long enough and high enough that bleaching was actually probably likely. Now, corals can recover their symbionts. If the temperature goes back down, they can reabsorb those algae symbionts and resume being a healthy coral. But if that temperature lasts too long and it's too high, that's a permanent ejection of the symbionts, and then coral reefs don't make it. So here is a list of 28 reefs total, and Hurghada, Egypt is one of them right here. So this is the list of the reefs, and in this kind of colored 3 rows here is the degree of coral bleaching. So no bleaching really only occurred in one little spot right here in Hawaii. Everywhere else either said that bleaching was possible, likely, or mortality was likely. So let's take a look and see if we see any trends in mortality likely. So if we just scan through these 3 columns, just on a quick visual capacity, we can see that there's more red as we go to the right. And in fact, in 2002, there's about 32% mortality likely. In 2010, 46, and 2014, 54%. Now again, on this year's AP exam, you will not be asked to do calculations, but you should be able to look at trends and to understand changes in the data. So we're seeing not only do coral bleaching happening, but we're seeing it happen more often in more places to the extent that mortality is likely. And if you want to look for a really great example of how impactful this is, look at some of the articles about the Great Barrier Reef in Australia. Really dramatic and saddening news there. So we've got this situation where we bleached this coral out, we dropped the biodiversity down really, really low. These corals are not going to recover. But so what? Well, really, this coral reef, like I said, is a habitat for many, many other species. It's breeding grounds for species. It's part of the food web. So this is going to have a really dramatic effect on the entire ecosystem there. So the standard says ocean warming is causing coral bleaching, which occurs with the loss of algae within corals, causing them to bleach white. Some recover and some die. So hopefully we've gotten through those ideas there. I do want to point out some very significant economic consequences. If I am this local fisherman and I am relying on the coral reef and the fish that live there for my livelihood, for my money that I live on, bleaching events are going to have a very negative impact on local fisheries, on my economic survival. So I want to go now and look a little bit at the scientific experiment practice. So again, these as well practices get more and more complex as we go through. So the first stage is, what's the purpose? What's the testable question or the hypothesis for the experiment? And then B and C really talks about what are their methods? How are they designing the experiment? I will point out that 4D is not assessed on the exam. That's because this is the kind of stuff that you would do in your classroom when you're actually making your own empirical observation. And then finally, the last part is, well, what could you do different to alter your results or to get different results? Kind of tweaking the experiment at the end. What I'm going to ask you to do is look at these 3 in particular. Can we identify the hypothesis or testable question? And then can we dissect and describe some of the methods used in an experiment? So to do so, we're going to look at an experiment from Dr. Palumbi. He is a researcher who studies coral reefs and is very particularly interested in the issue of coral bleaching. So he works in Ofu in American Samoa. He was the gentleman narrating the animation we just saw. And one of the things he noticed there that some lagoons were naturally warmer than others. So if you think about lagoons off of a beach, some are deeper, some are more shallow, some might get more sunlight than others. So some pools were just naturally a little bit warmer than others. And so he also noticed that in those warm pools, the corals seemed fine. They weren't being bleached out. So he designed an experiment to kind of figure out what was going on there. So I'm going to show you a clip, about a 2.5 minute clip. And as you're going through this, see if you can start to identify things like this testable question or his hypothesis, and can you kind of describe some of his experimental methods.
Coral reefs are one of the most spectacular ecosystems found in nature. Host to numerous biological communities, they are important havens of biodiversity and a valuable food source for over 500 million people. But as Earth's climate warms, so do the oceans, bringing heat stress to coral communities. When water temperatures get too warm, coral species may respond by expelling their symbiotic algae in a process called bleaching. Repeated or prolonged bleaching can lead to the death of entire coral colonies. Marine biologist Yves Plomby is studying how different coral populations respond to heat stress caused by warming oceans. He regularly travels to Ofu, a tiny island in Samoa, for his fieldwork.
Ofu Island and the lagoon behind the reef here is one of the best coral laboratories in the world. These back reef lagoons heat up to an extraordinary degree for a coral reef. They heat up to 32, 33, 34 degrees centigrade. That's above the temperature at which most corals will bleach and die, yet these lagoons are full of thriving, growing corals of many, many species. So the question is, how do these corals do it? How do they live in such warm temperatures?
To answer these questions, Plomby and his colleagues conducted a controlled experiment, devising a way to apply heat stress to the corals in the lab.
First, we had to build a standardized stress tank so that we could expose corals from different parts of the reef to exactly the same stress.
Plomby took corals of the same species from two different parts of the reef, one living in a warmer pool of water and the other in a cooler pool, and put them in the stress tanks. When grown and measured in these tanks, corals from the warmer pool were more resistant to bleaching.
So let's kind of see if we can analyze that a little bit. So for the first part of the science practice, it says identify a testable hypothesis or scientific question for an investigation. So let's think about the scientific question. So take 15 seconds or so and think to yourself, what was the purpose of that experiment? What question was he trying to answer? So the way I wrote it was, how does heat stress affect corals based on where they were previously living, either in a warmer pool or a cooler pool? And then in terms of the variables, the independent and dependent variables, take a second and think if you could define those two. So our independent in this case would be the home pool, whether or not they grew up in the cold or the cooler pool or the warmer pool. But the dependent variable is the amount of bleaching. How did they respond to the heat stress? And finally, what variables or what factors did he control throughout the experiment? So you can mention things like the living conditions. He set up the exact same cooler in the exact same way with the same type of water, used the same lamps, the same degree of heat stress. So everything was kept the same except for which pool they came from. So let's go back to Dr. Plomby for another minute and have him talk through those results a little bit more.
So this is the lab that we built in American Samoa. It may not look like much, but it's actually an incredibly important facility for us because we've been able to standardize the heat stress that we can apply to corals. We can provide them with a mimic of the kinds of heat they'll get actually on an Ofu coral reef and see how they react. So these tanks actually have heaters and chillers in them. They have lights. They have flow-through water systems. They're controlled by that laptop on the right-hand side. And we can use those little tanks to mimic what these corals will see during a very strong bleaching day out there in Ofu. Well, what do we see? We see this. We see corals that come out of the same tank looking very different. The coral on your left is bleached. It's lost most of its symbionts. The coral on the right, though, is not bleached. It came out of the same tank. It got the same heat. It's the same species. The only difference is that the coral on your left is living in a very cool part of the reef, but the coral on the right, same species, was living in a warmer part of the reef. So we know from this that different corals react differently to the same bleaching temperatures. Some bleach, like they're predicted to, but some are resistant to that. So the question that we really began to ask is, how do they do that? How do corals become resistant to bleaching? Does it happen quickly? Can all corals do that? That's why Ofu has been a really important research site for this.
So what he's getting at is that some of these corals that have grown up or that have evolved to exist in these warmer pools may have a range of tolerance for temperature that is different from others. And so looking exactly how that happens in terms of acclimation versus adaptation is a unique thing that he talks about later on in the video that if you wanted to peek at, you could. But the focus here is to understand the bleaching event itself. So that's ocean warming, and our phenomenon that we really anchored that on is coral bleaching. Now we're going to look at our second topic, 9.7, and this is on ocean acidification, and the goal is for you to explain the causes and effects of ocean acidification. So to get there, we're going to first describe the relationship between carbon dioxide and the acidity of the ocean, and then we'll look at some anthropogenic changes or anthropogenic activities that's causing this problem, and then look at some very specific effects, again, looking at corals and some other shellfish. So this is coming from last year's exam. So last year's FRQ number 3 says, the graph shows measurements of atmospheric levels of carbon dioxide at Mauna Loa Observatory in Hawaii, and measurements of pH in the ocean nearby its station Aloha. Measurements of pH began in 1992. So here's a graph, and this is what you're presented with at the beginning of the question. So we can see that on the y-axis, we have carbon dioxide parts per million, so the concentration of carbon dioxide. The years are on the x-axis down here, and we see this up, down, little wiggly line, but the trend is to get higher and higher and higher. So we can clearly see the carbon dioxide is increasing. But then the other little data set built into the same graph is pH. So from about 1992, the pH has also been measured in a wiggly line, but the trend is to decrease. Now those up, down wiggles are seasonal variations based on photosynthesis, but the overall trend is what we're interested in. CO2 is increasing, pH is decreasing. So we know that the ocean is a huge part of the carbon cycle. So NOAA says the ocean plays a critical role in carbon storage. It holds about 50 times more carbon than the atmosphere. And so we can see that carbon diffuses really easily into the ocean. So what's the main effect of that additional CO2? So having more CO2 in the atmosphere results in more CO2 into the ocean. And when it's absorbed by that water, it forms carbonic acid. And here is the chemical equation that represents that event. So carbon dioxide plus water yields carbonic acid. And there's a written form of the same equation. So therefore the pH decreases from the addition of the carbonic acid. So more CO2 in the air results in more CO2 dissolved into the ocean, which results in the formation of more carbonic acid, which drops the pH. This phenomenon is called ocean acidification. Okay, so we got ocean warming, and now we have ocean acidification. So what's going on here is this carbonic acid is causing problems with shelled organisms uploading calcium carbonate into their shells or their exoskeleton. So we've got this excess CO2 creating excess carbonic acid in the ocean, and this carbonic acid is going through some chemical equations or some processes that really just steals that carbonate away from the organism. So instead of the organisms being able to use calcium and carbonate to make the calcium carbonate is kind of sequestered off a little bit. But the main theme that you need to know here is that this is the result of the excess carbonic acid in the ocean. So this is part of that same question that we looked at before. C says changes in pH of the world's oceans pose a risk to many marine organisms. Explain why certain organisms, in particular those with calcium carbonate shells or exoskeletons, are threatened by the decreasing pH levels measured in seawater. So if I am a coral reef or if I am a bivalve mollusk and I am trying to get calcium carbonate to build my shell up, that ability is lessened because of the ocean acidification. So the answers to this would be, this is worth 2 points. 1 point for correctly explaining the impact of a decreasing pH on shells or exoskeletons, and 1 point for impact on the survival of the organisms. So you could say the decrease in the pH causes the shells to dissolve, and it's hard for them to add new growth or new calcium carbonate onto the shells. What does that matter? Well, it makes them less healthy. They're more at risk for predation or disease. They're not living optimally. So ocean acidification damages coral because acidification makes it difficult for them to form shells due to that loss of calcium carbonate. And just like with the other phenomena in the ocean, there are some severe economic impacts. And this is an interesting clip from a family of oyster farmers and how ocean acidification is impacting the business.
So we're cousins. Our dads are Bill Taylor and Paul Taylor, and they run Taylor Shellfish. And I'm Brittany Taylor, and this is Deani Taylor. And we're the fifth generation of our family to work for our family business. I really take pride in the fact that our company is part of a big community, and it's very family-like. We have many families, not only mine, but the other families that have their whole families that work for us.
The ocean is so acidic that it is dissolving the shell of our baby oysters. Our farm is what has kept this family together. It's our glue. I can't imagine it would be devastating to lose that such a big part of our history. When we started farming oysters over 100 years ago, we relied on the natural reproduction of oysters in the bay to occur in order to get our oysters. But as the industry has changed, we started cultivating our own oyster larvae, our own baby oysters. So when we started doing that, we needed something like our hatchery, which is kind of like a greenhouse, where you can raise up the baby shellfish, the baby oysters, to get big enough so that we can go and plant them on our beaches.
It took us a while to figure out what was happening in our hatcheries relating to ocean acidification, just because there's so many different things that can happen to make seed not survive. One of the things the hatcheries realized was that the clams and oysters were having problems forming their shell, so that made them look at the pH levels, because that kind of accounts for it.
We're going to pause there and feel free to watch the rest of it. It's really a great end of the clip. But clearly, ocean acidification is having an economic impact on this family's livelihood.
It's very vulnerable when it's...
So let's do a quick check for some understanding. So which of the following events would most likely lead to a decrease in the pH in the oceans? So hopefully you pick C, an increase in burning fossil fuels and power plants. Please make note of the word burning. A piece of coal by itself, just sitting there, is not going to decrease the pH in the ocean. But if that coal is combusted and creates carbon dioxide, that's going to get into the ocean, cause carbonic acid, and drop the pH. So be sure that if you're talking about fossil fuel use, kind of implicating that into an environmental problem, be sure you talk about the burning of the fossil fuel, coal, oil, and natural gas. Next question, coral bleaching can be hazardous to some fish species because... And the answer to that would be a big habitat for fish. So in summary, here's where we wanted to go today. We wanted to talk about ocean warming, and we just wanted to talk about ocean acidification and practice these two skills. Scientific experiments we did through looking at Dr. Columbia's work on in American Samoa, and then concept explanation we'll look at now. So let's just see if we got where we want to go with ocean warming. So we realized that ocean warming is caused by an increase in greenhouse gases. We know that that can affect marine species in a lot of ways, including loss of habitat. But in particular, we have this whole phenomenon, coral bleaching, that could kill a coral reef, and then all the subsequent biodiversity and habitat that would be there. So knowing these things on the right, can we then do this thing on the left? Can we explain the causes and effects of ocean warming? Absolutely. Let's go to acidification. Let's do the same thing. So in order to explain the causes and effects of ocean acidification, we need to know that CO2 is involved here. That CO2 is creating that carbonic acid, and as more CO2 is released in the atmosphere, it's getting into the oceans as well. What activities? We didn't spend a lot of time talking about this because I know this is something you've talked about before, and Ms. Fassler has mentioned it, but burning fossil fuels, vehicle emissions, deforestation, so the slowing down of the amount of carbon that we taken down for photosynthesis and sequestered in large forests. And then finally, going back to our coral reefs and other shellfish, they have a very difficult time forming their shells, and therefore we can explain the causes and effects of ocean acidification. So let's do an exam practice. So this again is asking you to do a concept explanation. So can you explain environmental concepts, processes, and models presented in written format? So you should be writing like you've taken the course, using appropriate vocabulary and depth of explanation. So this one goes again from more simple to more complex, kind of describing things and explaining things in different contexts. Can you use what you know in a novel situation or in a new situation? So our task verbs, I mention this every single time we meet, but the ones that we're going to mention today are identify, describe, and explain. So let's take a look at this one. It says coral reefs are produced when corals acquire calcium ions and carbonate ions from seawater and deposit solid calcium carbonate to form their exoskeletons. Scientists are concerned that relatively rapid decreases in ocean water pH will hinder the deposition of calcium carbonate. The graph above shows the amount of CO2 dissolved in ocean water and ocean water pH, shown in parentheses, since 1850, and the predicted changes through 2100. Two parts here that I want you to take about a minute to do. Explain how an increase in the amount of dissolved CO2 results in a decrease of the pH, and explain why that's happening. So I'll give you a minute and a half for that. And looking at the time, it looks like I'm running a little short, so I'm going to cut time a little bit. So the first question said, explain how an increase of dissolved CO2 results in a drop in the pH. So this is when we're looking for a statement like, when carbon dioxide dissolves in the ocean, it forms carbonic acid. Why is this happening? The concentration of carbon dioxide in the atmosphere is increased because of things like burning fossil fuels. B or D says, identify and describe a negative environmental impact from the loss of coral reefs. So let's go ahead and look at some of the answers. If I lose my coral reef, an environmental impact, not economic or societal, would be things like loss of habitat, loss of biodiversity, decreased protection from coastal or from storm surges, and loss of a carbon sink. And then you can see the descriptions here on the right-hand side. And finally, it says, identify one environmental problem other than one due to ocean acidification or loss of coral reefs that affect marine ecosystems. So now pulling away off of coral reefs, what other environmental problems are associated with marine ecosystems? And you can put anything from overfishing, increased ocean temperatures, invasive species, the eutrophication and hypoxic egg zones that we talked about the other day, plastic pollution in the ocean, oil spills, mercury pollution that Ms. Fassler talked about. Note here it says ocean acidification and loss of coral reefs are not acceptable because it said other than that. So just be sure you pay attention to the questions themselves. So once again, we know that not all students have access to the internet or a device. We're working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity or know someone who does, reach us at the URL below, and that's going to become more and more important. All right, everybody, thank you for tuning in for corals and ocean warming and ocean acidification, and I will see you next time. But right before I see you next time, Ms. Fassler is going to talk about invasive species and endangered species, so check that out. Have a good weekend.
Hi, good morning, APE students. Happy Monday. Thanks for joining us for another of our virtual lessons by the College Board for AP Environmental Science. Remember, we are still looking at Unit 9 on global change. We have just a couple lessons today and tomorrow left on that. And then we're going to start moving into some of the reviews, and we'll talk about that here in just a second. I'm Ms. Amy Fassler, and I am from Marshfield High School in Marshfield, Wisconsin. So before we jump into a quick warm-up and review from Dr. Sowell's lesson last Friday, I wanted to make sure that everybody's seen and been made aware of our exam, because the College Board has done an amazing job putting together an opportunity for you to take a legitimate AP Environmental Science exam. Remember, one of the reasons that we're going back and spending some time connecting all the learning targets from units 1 through 7 to units 8 and 9 is that colleges have been 100% on board with the College Board giving a somewhat modified exam. They just want to make sure you've gotten the full scope and sequence of the course. So as you may or may not know, our exam is going to be on Monday, May 18th. It's going to cover only the first 7 units. It's a 45-minute exam, including upload time. That consists of 2 free response questions, and you can see the layout of those there. Dr. Sowell is going to come back and talk more about this tomorrow as well. I just really wanted to make you aware of what we're going to be focusing on from here on out. Now that we've got a little bit more information, we're really going to focus on these science practices as we review all of the content in units 1 through 7, starting a little bit later this week. So we feel just so good about our ability to give you the knowledge and the skills you need to rock this exam on May 18th. So let's just quick focus on these first 3 bulleted learning targets. The first 2 notice are the same for both question 1, design and investigation, and question 2, analyze a problem and propose a solution. Question 1, the investigation's got a little bit more weight to it because we're going into that experimental design that we've looked at. We kind of really dug into that in the section we went over on toxicity and LD50. And then our second free response question is going to really focus on analyzing those solutions. So Dr. Sowell and I are going to be, every new lesson that we introduce or review, we're really going to be focusing, as we hopefully have throughout our time together so far, been focusing on those practices. So we'll keep coming back to that throughout the first few reviews that we do. So let's take a look at what you did last Friday with Dr. Sowell. Remember, we're in this unit 9 on global change, and you looked at a couple of learning targets that carried over what we learned about climate change and looking at the impacts of ocean warming and ocean acidification. Really interesting topics and exciting careers within the field of marine biology. So in general, you identify problems that are facing marine ecosystems on a global scale, and we're going to carry through or continue that conversation today by looking at some threats to ecosystems in general. We're looking to expand that out and look at freshwater ecosystems and terrestrial ecosystems, and that the topics that we're going to be discussing today, how entire populations can be impacted by these different aspects of global change. And then tomorrow, Dr. Sowell is going to bring Unit 9 kind of all together for us by looking at loss of biodiversity. So let's do a quick overview of what we're going to touch on in today's lesson. The learning targets are pretty straightforward. I'll break them down as we go through those 2 big targets, 9.8 invasive species and 9.9 endangered species. But remember, what we really want to try to work with are the skills and practices that we're going to be assessed on next month. So describing and explaining an environmental concept and process, using data to support a potential solution, and looking at advantages and disadvantages, or what we might call unintended consequences of some of those proposed solutions. So let's get after it. What do you need to know about invasive species? I'm going to go through that list of kind of the key essential knowledge statements that really describe for me what an invasive species is. They can live outside their normal habitat. So that's not to say that any animal that is outside their normal habitat is invasive. We further refine that description then and say they're considered invasive when they actually harm a native species. Some of the other terms we have for an invasive species, we call them non-native species to contrast it with the native species that are normally in that habitat, or alien species, something that shouldn't be there. They are typically generalists and classified as R-selected or an R-strategist species. You've heard about those before, and we'll be reviewing them in another week or so. But the key reason that we care about identifying them or classifying them as a generalist R-selected species is that has a lot to do with their reproductive potential and how rapidly they're able to get a foothold and then outcompete the native species. Oftentimes, remember, one big aspect of our practice today is to look at potential solutions, and many of the solutions we have for controlling invasive species really come down to some pretty kind of simple grassroots human interventions. So I'm going to kind of share this information with you by telling you stories about a couple of different invasive species, knowing that on a national exam, they would never ask me about one specific invasive species, and because there's a lot of them, and expect me to know all the nitty-gritty details of that one specific example. What we're going to try to do is look at a couple of different scenarios and understand that the ways that we describe how invasive species get into a new ecosystem, how they spread, and some of the strategies to control them are kind of broad-reaching and global and can be applied to many different scenarios. So we're going to start with the emerald ash borer. It's an invasive species that you may be familiar with depending on where you live. They can be intentionally or accidentally introduced. We'll look at that in a minute. They are a beautiful insect. This is the adult emerald ash borer. You can see it's this beautiful iridescent green color, and they were first detected in Michigan, kind of up here near Ontario in 2002. And just look at how rapidly they have spread and all of the states that they have now infested since that initial appearance in 2002. So one of the main things that all invasive forest insects do is that the female lays eggs in the inside of the tree, and those eggs hatch out into larvae, and those larvae then are going to burrow through the inner bark in the phloem. You don't need to know like a ton of detail about that. The big idea is that it's almost always something to do with the life cycle of that invasive forest insect and how that larvae eats through the part of the tree that's essential for transporting nutrients and water. And if that system is disrupted, obviously the tree is going to die. And then that larvae has to get out of the tree somehow to develop into that adult insect that's going to reproduce and lay more eggs. So remember I said they could be accidentally introduced, and one of the ways we think they were was through packing crates. So this maybe I ordered a new refrigerator and it came from Asia in this big wooden crate, and when the cargo ship got to a port in the United States, it dropped that off on the unloading dock, and maybe there was emerald ash borer larvae in the wood of that packing crate, and they crawled out, developed into that adult insect, and got a foothold in that new environment. Another way that they were somewhat accidentally introduced was through infested landscaping trees. One of the main reasons that ash trees were planted, or where we see an abundance of ash trees, is in urban areas. They're used in landscaping for people's yards. They're used on parkways and parks in urban areas, bordering streets. So urban areas have been hit really hard. And when we come back and look at forestry as we review that and forest management in another unit, we'll touch base a little bit on urban forestry and the benefits of maintaining urban forests. So as we look at how we're going to attack the problem of forest invasive species, one of the things we want to do is prevent them from ever coming in to begin with. So you might say, well, if I inspect that packing crate material, or if I monitor what the trees, like maybe I had a tree that came into my nursery that was infested, and it infested other trees in my nursery, and then I sold those to people, and they went home and planted them in their yard, and then the insects spread from there. So what if we want to, once it's been established, what if we want to sort of contain it? What are some potential solutions we can look at there? And again, this is kind of a general solution for any forest invasive species. And it's something we here in Wisconsin practice very closely, and that's banning the transport of firewood. In other words, if I pack up my car for the weekend and I'm going to go to a state park 100 miles away from here, and I take wood from my area, from my county, and then I get to my campsite and I drop it near my fire pit at my campsite in the state park, if there are emerald ash borer or larvae in my firewood, they can crawl out, develop into an adult insect, get a foothold, reproduce, and infect my entire state forest. So simply banning the transport of firewood is a pretty cheap, easy, and effective way to control the spread of this invasive species. It's what I call sort of a grassroots kind of down and dirty, right at the ground level of a simple, easy, effective way that I can control the spread of that. When you look at the disadvantages that I've listed here, it seems kind of like, well, that seems like it'd probably be a pretty easy thing to overcome. But when we look at past pre-response questions that have asked for students to present a solution, oftentimes the disadvantage of that solution is simply saying, well, it's really hard to get people to buy into this practice, or it's difficult to enforce. I might need a ranger coming and checking everybody's car or campground to make sure that they're not transporting or bringing their own firewood in. Just like right now, we're having a hard time having some people buy into the social distancing and staying at home as a solution to stop the spread of the COVID-19 virus. It doesn't work if you don't have really good buy-in. So again, a kind of a cheap, easy, effective strategy as long as we can get people to accept this as a strategy. Let's take a look at a couple others then, because again, I'm going to present some things that in general you might find helpful solutions on a broader scale to a broader range of problems. This one's maybe a little bit more specific, but what we see here is somebody actually injecting pesticide into an infected elm tree. So they're not spraying an entire urban area with a pesticide. They're really targeting exactly where that pesticide should go. So an advantage of this specific direct application technique is that in terms of using a pesticide, I don't have much of a concern about it spreading. Just trying to get it into the phloem of that specific elm tree where those larvae are once I know it's infested. The disadvantages of it mostly center around the disadvantages of using pesticides in general. There could be a resistance to that pesticide that develops, in which case it might not be helpful for me for any infestation down the road. So I want to be careful how much, and I want to use that technique sparingly. I could have human exposure and the toxicity effects of that, and I have the potential of killing a non-target insect. So there may be other nearby insects that could be impacted by that pesticide. This is a very costly process. So notice that my disadvantages range from everything to the toxicity of that treatment, to ecosystem impacts, to simply it may be beyond our financial ability to have individual people go to each individual tree that's infected. It may be something that an individual landowner might want to use. If I have old elm trees on my property, they're a big investment for the value of my home. They provide me a lot of shade in the summer, and I sit under them and have a picnic, and I enjoy the birds that nest in them for habitat. So as an individual homeowner, maybe that's a strategy that would be cost effective for me. This is a little wasp. This is kind of a creepy story, but it's in a general category of what we call using a biological control. So they're tiny, tiny little wasps. They kind of smell out the emerald ash borer larvae that for a tree that's been infested, and they burrow a little hole in there, and they deposit their eggs kind of on top of the emerald ash borer larvae. And then when those eggs emerge as larvae, they parasitize the larvae of the emerald ash borer. So it's just this kind of struggle for whose larvae is going to survive. So let's look at some advantages and disadvantages of a biological control in general. Again, I'm giving you kind of a cool story about these little wasps, but we want to expand that big idea to a broader, more global answer or solution that maybe I can use a biological control. Well, certainly the advantage is I'm not using any chemicals. I'm using something natural. So any of these disadvantages really don't apply. I'll come back to this as asterisk here in a minute. The biggest disadvantage is the potential for the organism that I introduce. So we know that these wasps larvae will parasitize emerald ash borer larvae. If they don't naturally occur where I have an emerald ash borer infestation, I could bring them in. I could introduce them, assuming that they're going to bore in and their larvae is going to parasitize the ash borer larvae. In general, we have a real big concern about using biological controls because that organism that I introduce to kill my introduced species could become invasive itself. Just to be clear, that is not the case with there's about 3 or 4 different species of wasps that they have found to be effective, and that's just not the case with this specific example. Once there are no emerald ash borer larvae, then the wasps die. Their eggs need that. Think cane toads, if you've seen the cane toad, about what happens when you introduce an invasive species. We have a couple other kind of general solutions. This is a trap that they set. So researchers and scientists are using scientific research in order to track where the emerald ash borer is spreading, how far can it go, how fast can it move, how much does it reproduce. So just getting all of this data and using my research and knowledge to help me develop sustainable solutions by understanding where the virus is spreading, where that insect is spreading, and how I can best control it. I can't really think of any disadvantage in promoting scientific research. So again, this can be used as a broad sort of solution if you can make it fit and justify that that's a valid solution. Notice I didn't just say do scientific research. So that I want to add that little bit about why is doing scientific research a good solution, because it gives me data and information about where the invasive species is, how fast it's moving, how fast it's reproducing, and then I can really target my intervention strategies. And one other final, very broad general solution that we see oftentimes is raising public awareness, like we talked about with banning the firewood, or what we sometimes call educating the public or increasing public awareness. And certainly one of the advantages that I kind of mentioned is that healthy trees are healthy people. We can often get people to buy into this because they value the either for ecological or economic or aesthetic or biophilia. They feel good when they have those trees to connect with, or simply that they really add value to my property because I've got this beautiful mature landscaping. If I raise public awareness and get people to understand the value of the tree, we tend to preserve what we cherish or love or value. And if I understand and value that tree, I'm more apt to work to preserve it. So this is a common practice. I believe this is a signage from New York, but they simply label volunteers often will label a tree saying, hey, I'm an ash tree and I'm really susceptible to being invaded by an emerald ash borer. Here's some things that you can do to educate yourself and help save ash trees. I know that in our community, Boy Scouts have taken on that project for Eagle Scout projects to go around and label the ash trees. So let's take a minute and kind of step back and clear up a couple of misconceptions about forest invasive species and make some connections about where we're going to go after we look at invasive species. So I'm going to share with you a quick story about the mountain pine beetle in Yellowstone. If you've not yet had the opportunity to visit our oldest national park, first established national park in the country and I believe in the world, Yellowstone is located primarily in the northwestern corner of Wyoming, but it kind of creeps into Montana there a little bit. There's an entrance up in the Lamar Valley near the Montana border, and we'll actually go back to the greater Yellowstone ecosystem a little bit more next week. So let's take a look at what's going on with the mountain pine beetle in the Yellowstone ecosystem. You are going to be hearing from Dr. Elizabeth Hadley in this video.
Why
bark pine produce very high nutrient seeds. The bears will come here right before they go into hibernation, and this is when they really pack on a lot of fat in order to overwinter. The nutrients from those seeds is directly correlated with overwinter survival of bears.
But grizzly bears cannot reach most of the pine cones because they're too high up on the trees. So they rely on a smaller animal for their snack. Red squirrels easily get up to the pine cones to eat the seeds, storing the excess in ground burrows or middens.
All around us are middens from squirrels, and this is what the bears go after. And indeed, here is a pile of bear scat, and in the scat are seeds from white bark pine.
These three organisms, the tree, the squirrel, the bear, represent a healthy food web. But a tiny creature is threatening the survival of all three organisms.
Okay, Sean, this tree has been hit by the mountain ivy. What happens with these? What you see, the evidence are these little holes. What happens when you see this kind of response on part of the tree is that the beetles won. This tree's dead.
How old do you think this tree is?
This tree, probably 700 years or so.
700 years. And how long does it take the beetles once they attack to kill a tree like this?
So once they attack, this is a big attack. It's a day or two.
A day or two.
A day or two.
After 700 years.
After 700 years.
The beetle has always existed in Yellowstone. It's not a foreign species. What has changed is where and for how long it survives.
The warming climate in this high elevation region is allowing beetles to move into these what were previously high elevation cold regions. And now they're high elevation, it still gets cold, but it's not cold enough to kill beetles. So they're surviving longer and killing white bark pine.
So what a really cool story to show us those connections. So invasive species like the emerald ash borer that is it's only killing ash trees. But if I don't have an ash tree, I don't have the nesting sites for the birds that live there. The key thing that I want you to catch from that big misconception, is that the mountain pine beetle is not invasive to the greater Yellowstone ecosystem. However, because of a warming climate, cold winters that normally would have killed the larvae of that beetle are allowing them to survive. So it's almost kind of like we've turned it into an invasive species through our actions that have led to a warming climate. And what we're going to transition to in a little bit is looking at grizzly bears as an endangered species. So we'll come back and make that connection. Let's look at another story of another type of invasive species now that we kind of have a general idea of forest invasives. And even though you saw mountain pine beetle, not the emerald ash borer, remember that the impact of that and how it impacted the tree is somewhat the same process for all forest invasive insects. So next let's talk about some aquatic invasive species. And these are freshwater aquatic invasives, the Asian carp. If you have never heard of Asian carp, I'm just going to show you a quick video of them. They're pretty amazing. There are a couple of different species. These were purposely introduced in the southern United States, and they were used in like a fish farm, an aquaculture facility or farm ponds because they're algae eaters. They're low on the trophic level eaters. They eat a lot of plankton. They eat a lot of aquatic vegetation. You'll see in a minute, they're a pretty good sized fish. They weigh a lot, and there's a lot of nice white meat on that fish. So what happened is after they were purposely introduced to kind of control algae growth in an aquaculture, well, then there was a big rain event and it flooded and all that water overflowed, and they escaped from those ponds or containments that they were in, were able to enter the natural aquatic ecosystem through the series of lakes and rivers, spread very quickly, reproduce very quickly. Remember, these are our strategists, and were able to outcompete the native species. So here's just a quick video of kind of an interesting characteristic of Asian carp. These are scientists who are doing some research. So obviously one of the problems with Asian carp is that you could get hurt if you're out on the river and you're fishing and those Asian carp come out, they could really whack you and really do a number on. So let's talk about some of the solutions. So you kind of saw me to show you again this previous map. This is kind of how the Asian carp has spread natural waterways through lakes and rivers. Well, up here in the Great Lakes region, we're really concerned about the Great Lakes entering because all my lakes are connected here. And the reason we're concerned is that Asian carp can affect the $7 billion per year industry, fishing industry, and recreation industry in the Great Lakes. So this specific example of a solution is a much more aggressive approach than some of the more grassroots kind of simple solutions that we took a look at for forest invasives. Here is the waterway where the Asian carp are working their way up. And what they've actually done is constructed this series of locks where they can raise and lower the water level. And they put kind of like electric gates so that if the carp, there's a passage there preventing the carp from getting in to Lake Michigan. There's these electric fences and gates. There's everything they like are blowing bubbles and making noise to deter them. This is a very expensive solution. It's in the hundreds of millions of dollars, but the economic impact of Asian carp wiping out the native fish populations, which we have evidence that they would do, is worth it. There's a really big push on a national level to try to get funding to control the spread of the Asian carp and prevent them from entering the Great Lakes. But let's take a look at how we can use some of those simpler, more grassroots approach to preventing aquatic invasives. We here in Wisconsin, as I know many of you do, love our natural and scenic rivers and our beautiful waterways that are a source of revenue for tourism and business and simply enjoyment for those of us that have that connection to aquatic systems and like to get out and enjoy the water. So one of the things we've done is on the 4th of July, when there's a lot of boats out on the water, the Department of Natural Resources organized what they call the landings at a boat landing. This was all volunteer work. Volunteers were educating the public. They were standing right at the landing and handing out brochures and showing people how they clean their boats and their gear and the importance of doing that to prevent the spread. And again, we have a pretty captive audience here because these are people that are out enjoying the natural waterways and have an investment, a reason to want to stop the spread of invasive species. So in general, if I wanted to provide some specific solutions, things like cleaning off my boat, if there's any aquatic, even an invasive plant, an invasive weed, any little speck of that that's hooked on part of my boat, zebra mussels that can actually suck onto the side of my boat, any aquatic invasive when I take my boat out of the water and I take it home and the next weekend I go to a different lake, I might be introducing an aquatic invasive from the lake the first weekend into the lake the next weekend, the different lake the next weekend because I didn't clean my boat or I didn't clean my gear, or maybe I had a bait bucket in the water and the water that my bait was in had some aquatic invasives in it and I dumped it out. In general, people dumping aquarium species into the water, so not releasing fish that don't belong there. And again, a lot of this really comes back to educating the public. And you often will see signs right at the boat landing now encouraging people to participate in this simple practice to stop the spread. The same general idea applies to terrestrial invasive species. If I'm out hiking or biking in the woods, there could be something there could be plant spores that stuck to my boots, or there could be something on the mud of my boots that I walk through, or my bike tire. So that same idea, cleaning your gear, removing and hosing down those mud boots right away before you take them on another hike in another place. And then we'll look at one more example of an aquatic invasive. This may look familiar to you. It's a lionfish. And another solution is to simply turn these invasive species into food. So the lionfish is native to the South Pacific and Indian Ocean, and it became a popular fish that was sold in aquarium stores in the 1980s in the Florida region. And then either people dump their aquarium fish into the ocean, or aquarium owners just thought, people don't want to buy these anymore, I'm just going to get rid of them. And like many invasives, without a natural predator in that fine-tuned ecosystem, they quickly spread, reproduce as our strategists will, and it reduced native species populations by 90%. So we have an ecological, I would argue a human health argument for eliminating invasives because they destroy the natural beauty of an ecosystem that I personally want to enjoy, and certainly an economic impact. So what a lot of restaurants are doing is they are harvesting these and selling them, putting them on the menu, both in Central America and in Florida. So let's talk. Remember when we looked at our little objectives, the little essential knowledge statements right at the beginning? We really wanted to tie the characteristics of an invasive species to the characteristics of an R strategist. So they have many offspring per year. That's one of the reasons they're a successful invader, is that their population grows very quickly. They're generalists in terms of their habitat and food requirement. So especially as humans alter natural ecosystems, if I have an area that I have clear cut, my native species are like, oh, I can't live there. There's no mature trees that I need for my habitat, or my food source has now disappeared. But an invasive species says, whatever, I don't care about soil conditions. I'll eat whatever food there is. So when we disturb an area, it's really easy for them to get a foothold and take over and outcompete the native species. And of course, climate change means more invasive species. Severe weather events like flooding and high winds and habitat disturbance may damage native ecosystems, opening that door to invasives. So let's do a quick check for understanding. This is a release free response question from a few years ago that shows a map of the spread of the zebra mussel. That's the one I had just mentioned. It's a mollusk native to Eurasia, first discovered in the Great Lakes in 1988. The recent range of zebra mussels is indicated by the shaded area of the map. Adult zebra mussels can survive for several days or even weeks out of water if the temperature and humidity are favorable. And adult zebra mussels female zebra mussels can produce as many as 1 million eggs per year. So I'm going to give you a minute to answer 3 quick prompts. Describe how zebra mussels were introduced into isolated lakes. Describe one viable method for preventing the spread of zebra mussels into isolated lakes. And one potential strategy to reduce the population would be to introduce another species to control it. That idea of biological control. Describe a potential consequence of that strategy. I'll give you a minute to work on that. So describe how zebra mussels were introduced into isolated lakes. They could have been transported by boats, as we talked about. They could have been transported by animals, maybe even waterfowl. Maybe one of those little mussels kind of got in the feathers of a waterfowl. They could be brought in by fish stock. So kind of a lot of the mechanisms that we already talked about. One of the ways to prevent the spread of the zebra mussel, again, a number of those strategies that we looked at: flushing or draining water from my boat, cleaning my boat before transferring it, and then information campaigns that just discourage people from those practices that would spread it. And then a potential consequence of this strategy, all of these are kind of the same. I started them out all the same. You can look at how you responded to it. But a potential consequence could be that the zebra mussel might prey on non-target native species. The organism I introduced to control the zebra mussel might prey on other valuable species in that ecosystem. The zebra mussel could compete with the native, the organism that I introduced could compete with native species for resources. The organism that I introduced could be toxic to predators or reduce the food supply for predators. And then remember, this is kind of that one that said, like, remember where we look at, even though the mountain pine beetle wasn't per se invasive, we get this idea that many of these invasive pest species have broad ecosystem effect. They can cause a disruption or alter the entire food chain or biogeochemical cycle of an existing ecosystem. So let's move on to our last learning target for today. And then Dr. Sowell's going to pick up with this tomorrow. We're going to look at endangered species. And here are the essential knowledge statements that we want to know about that. There are a variety of factors that lead a species to become threatened with extinction. Species that are quickly able to adapt to changes in their environment are less likely to face extinction. Endangered species tend to be K strategists. So invasive R, endangered tend to be K strategists, and therefore are going to have a hard time recovering if their population declines. And strategies to protect the animals include protecting their habitat, wildlife management, criminalizing poaching, and legislation. We're not going to get into this a lot today because Dr. Sowell's really going to pick up with that tomorrow. So I just want to share a quick story with you about an endangered animal, the African elephant. Elephants are K strategists, and I want you to be able to make the connection about what it is about being a K strategist that lends itself to making me prone to extinction or being endangered. Well, remember, K strategists have very few offspring per reproductive event. They expend a significant amount of energy raising that offspring. They feed it, they protect it from predators. They will often, the mother may die in an attempt to save their young, and they mature after many years of extended youth and parenting. So they themselves don't reach reproductive age until much later in life. Unlike a mountain pine beetle, that the minute that hatches out, its job in life is to reproduce, and then it dies. So let's take a look at a quick story of what's happening to African elephants. There we are.
African elephant populations are severely threatened from habitat loss and from poaching fueled by the international ivory market. We're losing elephants at an alarming rate. The statistics that are coming are 100 elephants a day. Scientists estimate that in the 1970s, the area occupied by elephants spanned the African continent and included 1.3 million forest and savanna elephants. Today, the known elephant range is much smaller. How many elephants remain and precisely where they live is not clear. Collecting this information will help focus conservation efforts on areas where elephants are in danger.
It's extremely important for us to get these numbers right because they go straight into management, and they let the managers and the politicians decide how to actually intervene with what's going on in a particular area.
A very sad and tragic story, but as we progress, you'll see that there are things being done to try to protect African elephants. I wanted to focus on the last part of that short clip where they said that they're kind of introducing this idea of this big census that they're going to do, where they have this amazing multinational funded project to get an idea of the count or what is the current population size of African elephants in a greatly reduced habitat. Remember, that comes back to that idea, that solution of promoting scientific research. I can't have a management strategy for preserving the elephant if I don't know what the numbers are, where they're being poached, how many are being poached, how many offspring are being born. So all of this is essential in planning a strategy or a solution. So let's kind of go through a guided practice question, and then we're going to wrap up with a question that I'll leave you a little bit for homework that you can look at with Dr. Sowell tomorrow. So we've already looked at, I think when we looked about infectious disease, we touched on 1 or 2 topics for this white-nose bat syndrome question. I just have one prompt here that we're going to walk through together. Let me give you the background. As another winter concludes, biologists are alarmed by the continued spread of white-nose bat syndrome. White-nose syndrome is a fungal disease that has decimated populations across eastern North American forests, where mortality rates have reached up to 100% at many sites. White-nose syndrome has been found in at least 25 states and in 5 Canadian provinces. If the little brown bat species does not become extinct and can potentially recover, the rate of recovery is likely to be slow. Discuss one aspect of bat biology that might slow the recovery of the little brown bat population to pre-white-nose syndrome numbers. So make sure you understand what the question is asking. We've got something, we put a solution in place, and we're starting to see the little brown bat population rebound. It's starting to come back. But one of the problems is that even if we can prevent it from going extinct, something to do with this biology might slow that recovery. So if you remember, one of our skills that we wanted to practice was to be able to describe an environmental process or concept using information presented in written form. And they gave me a bunch of background information about the little brown bat. So white-nosed bats have a low reproductive rate. There's a number of ways you could say that. They have few babies per year, a long generation time, advanced age at reproduction, And thus, if the population declines, it will have a hard time recovering. Here's a misconception or an area that students didn't quite communicate that idea clearly enough. They simply said, well, white-nosed bats have, they're case strategists, so they don't reproduce a lot of offspring. If I simply said they don't produce a lot of offspring, that's a characteristic of the little brown bat that they've always had. Why would all of a sudden having a small number of offspring be a problem? This is the key part of that sentence that earned the student the point. It will have a hard time recovering. If I simply said the part of their biology that will slow the recovery is that they have a small number of offspring, it wasn't enough because they always have a small number of offspring. And that is, this characteristic is what is going to give them a hard time to bounce back from that. Another characteristic of case strategists is that they can provide this care for their young. And if the parent dies and there's no one to care for the young, there's a greater chance that the offspring will not survive, thus presenting further challenges to the recovery. So let's take a look at an exam practice question that I'll leave you with today. We'll look at the first part of it, and then I'll introduce what you're going to do tomorrow with Dr. Sowell. So here's another pre-response question about endangered species. Populations of large terrestrial mammals, such as African elephants and snow leopards, are in decline around the world. Many of these animals are now on the verge of extinction. And there was a little bit more there that went into some topics we're not going to focus on. The first prompt asks you simply to describe the relationship displayed on the graph. And then what I want you to do for homework is letter B. Identify a characteristic of a case strategist and explain how that makes it prone to extinction. Make sure that that you try and do that letter B as practice, because the model Dr. Sowell and I are going to use going forward is for you to, instead of just quickly trying to scribble something down and give you a quick answer to it, we want to start moving into giving you a little bit of practice on writing those FRQs. Now that we know what our FRQ national exam is going to look like, you're not going to write big full 25-minute FRQs every night. You're going to try to model like 10 minutes of a quick exercise, parts of a potential response, and then we'll check in with it on the next day. So let's see if you can first of all describe the relationship on the graph, and I'll give you just a minute to do that. So here we're following that skill, analyzing visual representation of data. And there's a number of ways you could have stated this, but the graph basically shows the change in elephant population over time. And I can see that the elephant population declined quite dramatically for a number of years, but then it showed that it was starting to increase and level off. And you can imagine that the next part of a prompt may ask me something about why the population was in great decline and maybe what happened that caused it to start to go up again. Those are some of the topics that you're going to take a look at tomorrow with Dr. Sowell when you look at preserving biodiversity. You're going to dig in a little bit more deeply on some of the causes for animals becoming endangered and certainly some of the solutions. And I just wanted to make sure that we kind of checked in on our learning targets for today. So here are the practices or skills that we decided we were going to focus on and how we demonstrated our knowledge or understanding of that. And the same thing with that, providing a solution to an environmental problem when we looked at the zebra mussels. Just to make sure everybody caught this information about where you go. If you need assistance with a mobile device for the national exam, you're going to be able to use any kind of device, computer, tablet, laptop, cell phone. But we just want to make sure that you have plenty of heads up on that so that you're going to be good to go when May 18th rolls around. Thanks for joining me. Have a great day tomorrow with Dr. Sowell, and I will see you again on Thursday.
Hello, APES. Welcome to our online lesson for today. So my name is Dr. Sowell, and I teach APES, AP Environmental Science, down in Jacksonville, Florida. So just a quick update. I mentioned this the other day, and I know Ms. Fassler has as well. The details of our exam are now out. So we'll be taking our exam on the 18th of May, and you can see the times there on the screen. And we do know the details of the two FRQs. We know that FRQ number 1 will be the design and investigation. That's the name of the question. And then question number 2, which is 40%, is analyze the problem and propose a solution. And underneath each of those descriptions, you can see the types of skills and practices that you're going to need to be able to do in order to successfully earn points on those questions. So something to review. All right, a little bit of a warm-up. So yesterday with Ms. Fassler, you really talked about two things: invasive species, like this emerald ash borer, and she explained some key characteristics that make an invasive species particularly impactful in an environment, such as being an R species or not having any predators per se. And then she also talked about endangered species, and again linked that to some of the characteristics, such as a case species. So we had invasive species and endangered species. And she left you with some homework. So let's go over the homework. This was part of the question. It said most large terrestrial mammals are case strategists. Identify one characteristic of a case strategist, and explain how that characteristic you identify can make those mammals prone to extinction. So there was an identify and an explain. So check your answer to see how well you got this. So some of the characteristics are having a low reproductive rate or producing few offspring. And here you can see there's some explanations of why that might make this organism more prone to extinction. For example, difficult recovery from population decline or fewer chances to pass on their genes. And then there's a couple of other characteristics as well about long gestation period, parental care, late age first reproduction. But remember, there's two parts of this. You identify the characteristic, and then the second one comes from you explaining how that characteristic makes them prone to extinction. Not just explaining the characteristic, but how that ties into their being more prone to extinction. So let's look at a student sample here. So this student wrote, elephants, case strategists, produce few offspring with an extended period of parental care. By producing few offspring, a population can die in just a single generation because the offspring have a much lower survival rate than our selected species such as dandelions that produce many offspring with the idea that some will die, but the ones that live will carry on the species. So this person received 1 point here for identifying that elephants as case strategists produce few offspring. However, the rest of their description didn't connect that to how they are prone to extinction. They went into some more details of what an R selected species is, but really didn't go into that explanation point. So they got 1 point for explain, 0 points for identify. Now let's take a look at part E. He says identify and discuss, again, 2 parts, 2 conservation strategies that could be implemented to prevent the extinction of large terrestrial mammals such as the African elephant or the snow leopard. So again, you have to identify the strategy and discuss how that could be implemented to prevent extinction. So there's lots of answers you could have written here in terms of enforcing laws, education, captive breeding programs, but whatever you identify, you also have to discuss how that strategy could be implemented in order to prevent extinction. So let's take a look at a student example. So this person said, in the case of the large terrestrial mammals, many are endangered due to human overuse poaching. If the value of the fur, tusk, etc. was eliminated, poaching would possibly stop. For example, if an African elephant's tusk was discolored, it would have no value and the elephant would not be killed. So this person definitely gets the point for identifying the action and how that could be used to reduce extinction. But they only listed 1, so they got 1 point. So this is going to be kind of Ms. Fassler and I are going to do throughout the rest of the sessions that we do. And so she will leave you with an FRQ question and I will help answer the day after and vice versa. So today with me is the last day of new stuff, new content. So this is the very last topic for Unit 9. Starting tomorrow, we're going to go back to Unit 1 and start reviewing. So we start with ecosystems, go into biodiversity, populations, our earth systems and resources, then land and water use, energy, and finally atmospheric pollution. So starting tomorrow, we will start going through these so that by the end of the review period, we'll have covered a vast majority of what's in those units. All right, so where are we going today? We are looking at one particular topic 910, human impacts on biodiversity. And through doing that, we will practice science practice number 7, environmental solutions. Because remember, this unit is all about identifying human impacts on global change, and then what are some solutions or what are some strategies to prevent those problems from happening in the first place or to mitigate their effects. So I will kind of take a nod back to two previous units that you may want to take a peek at in order to fully understand this. Number one is the introduction to biodiversity. What is biodiversity? And the second one is island biogeography. This is unit 2, topic 2. It will come to play a little bit here in this lesson, but I know that Ms. Fassler has already has plans to really go into depth on island biogeography when it comes time for that review. But these are the two previous units that will come play with today's stuff. All right, so what you need to know from 910. The whole goal of this is you should be able to explain how human activities affect biodiversity and strategies to combat the problem. So we've got a grizzly bear here, and so to get to this learning objective, to be able to do these things, we are going to quick review of biodiversity. We'll spend a lot more on unit 2, but I'll do a quick review of it here. Talk about the main factors leading to a loss in biodiversity, a decrease in biodiversity, and explain the causes and effects of a particular thing called habitat fragmentation, and then some conservation strategies that might mitigate that impact of biodiversity loss. So that's where we're headed today. So just a quick nod back to unit 2, developing an understanding about biodiversity. So this starts it off by saying biodiversity, which includes genetics, species, and habitat diversity, is critically important to ecosystem. And we'll take a quick look at each of those three things, but it's important to realize that we don't want biodiversity just for the sake of biodiversity. It plays a very important role in the stability of an ecosystem. So topic 2, introduction on biodiversity, starts with those 3 layers of biodiversity: genetic biodiversity, species biodiversity, and habitat biodiversity. So the first one is all about the variation within a gene, within the genes of a population, and how that kind of gives them an advantage, an evolutionary advantage to better adapt to environmental stressors. Ecosystems that have a large number of species are more likely to recover from disruptions. So there's an important role of biodiversity at the ecosystem level. Then it goes into talk about how certain species react to these disturbances. It also leads to a reduced number of species and large territory requirements. So if you're an organism that has a large territory, it can affect you a little bit more. And finally, just define species richness, which is that species biodiversity. I do want to point at one particular one here about the number of species and disruptions. This really points to ecosystem stability. So if we have an ecosystem with a large species biodiversity, it's more stable. It's able to resist stressors, and also if they do happen, to bounce back from them. So therefore, biodiversity loss impacts stability. So when we talk about all the things that lower biodiversity in an area, yes, it's affecting food webs and food chains and energy flows and all of that, but it's also affecting on a broader picture the general health and stability of the entire ecosystem. All right, so here's a question I want you to ponder throughout today. So what are some conservation strategies you could use to ensure a healthy grizzly bear population? So take a second, take 12.5 seconds, and think about what you would do if you were charged with ensuring that the North American grizzly population was healthy. All right, keep those ideas in mind as we move forward. So the first thing we're going to do is look at how we're losing biodiversity. So there is an acronym called HIPCO, and that each of those letters stands for one of the main anthropogenic causes of biodiversity loss. There are some natural causes, but what we're focused on here that human-induced are anthropogenic causes. So H stands for habitat destruction, I stands for invasive species, P stands for population growth, P also stands for pollution, C stands for climate change, and O stands for overexploitation. These 6 things are 6 categories that have the most impact on biodiversity loss from a human perspective. Now we're going to go through briefly each of these, but you're going to notice I'm going to start with I and then go I, P, P, C, O. And I'm going to say H for last because that really forms the basis for the majority of the conversation in this particular topic. So let's start with invasive species. Like I said before, Ms. Fassler did a phenomenal job of giving you some characteristics of invasive species, some of the solutions, and maybe some of the unintended consequences of some of those possible solutions. So for example, we've got the lionfish here down in Florida. We know that lionfish is a very bad invasive species. It was first noticed in the 80s here in Florida, and it has no predators down here. It's an R strategist, so it's cranking out little lionfish left and right, and it has a voracious appetite. So it eats a lot of little tiny small fish, and because of that, a lot of those small fish are primary consumers. They're eating algae and plant growth underwater. So without those smaller fish, algae growth kind of takes over a little bit, and then they also outcompete those larger fish for those smaller fish. So we see loss of biodiversity in terms of large fish, and clearly that has an economic impact for fisheries. So yes, you need to understand what invasive species are, but you need to be able to also connect that to biodiversity loss in general. P, population. There's a lot of us, and we keep making more of us. So in unit 3, we're going to really talk about the dynamics of the human population, and we will go into some very concrete effects that increase in population has on the environment. It's not just our numbers, but it's also our manner of consumption and use of natural resources. So we'll save a lot of that conversation for unit 3 review. Pollution. I think this is a no-brainer. Pollution's bad. Pollution kills organisms, but also pollution destroys habitat. So we can see, for example, this is an oil spill. This happens from the Deepwater Horizon oil spill in the Gulf of Mexico, and you can see clearly some impacts on wildlife here, such as the bird, and Ms. Fassler touched on that as well. Climate change. Clearly, climate change is going to affect biodiversity. We can see changes in precipitation and temperature or sea level rise, and that can either wipe out a habitat or fragment a habitat or cause a population to shift its range. I mentioned this the other day about the lobster population shifting north in response to warmer waters. So another example that I gave the other day was coral bleaching. So we see the climate change causing sea surface temperatures to rise and the corals expelling their photosynthetic symbionts and becoming bleached. So the entire rich biodiversity of the reef crashes down because of climate change, because of coral bleaching. And then overexploitation or overharvesting. This is just us taking natural resources at an unsustainable rate. Famous example is the passenger pigeon that we hunted to extinction. They no longer exist on the planet. The current problem, and this is something Ms. Fassler mentioned the other day, is elephants being poached, being hunted. So one of the solutions to that is CITES. So this is the international treaty to ban the trade and sale of endangered species or their products such as ivory. So there's an example of a solution that can be applied to this overexploitation problem. So let's circle back to habitat destruction because that's where we're going to spend the most of our time today. But I do want to be a little bit more nuanced and talk about habitat loss versus habitat fragmentation. They're both involved in the destruction of habitat, but when I say habitat loss, I just mean there's less of it. So for example, in this picture, if I was a woodpecker and I was living in this forest and then it was clear cut, well, I've lost some of my habitat. I could still fly over here and use that habitat, but the amount of habitat available to me is less. But another consequence of that is the fact that what is left is broken up. It's in pieces now, and that has a very unique strategy to mitigate it or to solve it. So let's take a little bit deeper look at fragmentation. So again, habitat loss is just what's gone. Habitat fragmentation points to the problem of what's left because it's all broken up. So let's take this snake down here. This is the indigo snake. This is one of our native snake species down here in Florida. Really big, large, shiny, black, non-venomous snake, gorgeous snake. And its habitat is represented by this blue box. And the habitat happens to be very upland, xeric, turkey, oak, pine, scrub areas. But if we come in with development in terms of roads or buildings or shopping malls or convenience stores, we start to chop up their habitat. So you'll notice what's left of the indigo snake's habitat. Not only is there less area, there's less habitat, but they are separated from each other. They are fragmented. So habitat fragmentation occurs when large habitats are broken into smaller, isolated areas. Causes of habitat fragmentation include the construction of roads and pipelines, clearing for agriculture or development, and logging. So you might think, well, okay, that's an issue, but what's the particular problem with that? Well, it can also happen in the water as well. So if we think about this hydroelectric dam, if I was a fish and this was my habitat, now my habitat is fragmented, or a turtle, my habitat fragmented. And it also matters the scale of the organism. So I want you to imagine a grizzly bear, big old giant grizzly bear, versus a little anole, these little green lizards we have all over the place here in Florida. They have very different home ranges. The home range for this grizzly bear might be over 600 square miles, as opposed to this anole, Anolis carolinensis, might only be my front yard, maybe only up to 100 square meters for a lizard. So when we talk about habitat destruction, we also need to remember the scale of that destruction, what it might mean for different organisms. So I'm going to be showing you a couple of clips from a documentary from Howard Hughes Medical Institute Biointeractive, and I will be stopping and starting along different ways as we go through this issue of habitat destruction.
Not long ago, most of Earth was covered in vast wilderness, rich in biodiversity. As human populations expand, habitats are shrinking and becoming more fragmented. many animals now face a new kind of struggle to survive. How can we protect the wildlife and wild places that remain? One of the foundations of conservation, now being applied across the world, began with the dreams of a young boy in Mobile, Alabama, and of all things, his love for ants.
So this documentary really goes into some of the foundational work of E.O. Wilson and his theory of island biogeography. We're not going to watch that part of it because we are going to save that when we cover it later in previous units. But today I want you to be thinking of this issue of habitat loss, habitat fragmentation in terms of scale as well, from something as small as an ant to as big as a grizzly. So again, let's revisit the idea of habitat fragmentation. So if we look at these two landscapes, we can clearly see that there's still some habitat, there's still some green spaces, but they're quite separated from each other. And even if they are there, they may be just turned into agricultural land and not be suitable habitat at all. But again, why do we care about this? Not only am I losing habitat, but it's fragmented. And what does that do? It may not give me the amount of home range that I need, and it may kind of reduce my success in feeding or mating, finding mates, so the genetic diversity of the population might suffer. And again, this goes back to E.O. Wilson and his ideas of island biogeography, and that's from 2.3. And the connection is this: he studied, in a nutshell, how biodiversity happens on islands in the ocean. What makes one island more or less biodiverse than another island? And so what conservationists on land have done is extrapolated those ideas to something like a national park, which in essence is an island of natural habitat surrounded by human development. So let's continue the story and kind of take that jump from the islands to the mainland.
The world can be viewed as a series of islands, fragmented by human beings.
Farms, roads, and towns are steadily shrinking Earth's remaining natural habitats, creating islands in a sea of humanity. Do these islands on land behave the same way as Wilson's tiny mangrove islands? To find out, in 1979, conservation scientists launched a landmark experiment in the Amazon by carving the rainforest into different sized patches and monitoring biodiversity.
One of the most important things that the project found is that these fragments really do work as islands. They function as islands of forest that's surrounded by pasture. The effects of fragmentation are really strongly felt by the monkey species. They spend all their day and night up in the trees. It's very rare to see them come to the ground. And when you start to isolate the forest, resulting in these forest fragments, then these monkeys basically get stuck in there. There are only 2 or 3 species in these little islands, as opposed to 6 in the continuous uncut forest.
The smaller forest patches supported fewer species. But the experiment also revealed an important new finding, something Wilson could not have seen on his mangrove islands that only contained tiny animals.
The larger species are more affected just because they have larger range requirements. They need much more area. So things like jaguars, harpy eagles, spider monkeys. When the forest is cut and then we leave these little isolates of fragments, then we start to see some of the species dying out.
The Amazon experiment sounded an alarm. It showed that shrinking a habitat has a greater effect on larger animals.
So when we go back to that original question I asked you about conserving the grizzly bear, that should start you thinking about how saving a grizzly bear population might be a little different from saving a lizard population or an ant population. So scale and size really matter here. So if you think about how you're going to save the grizzly bear population, that might be a little different than saving a lizard population, for example. So this is going into science practices. So when we start thinking about solutions, remember we have to first understand the problem. So we've understood what habitat fragmentation is, and now we've got to start generating some possible or potential solutions that are realistic, and then finally being able to justify one of the solutions that you do propose. So one solution might be protected areas. So making green spaces or parks within cities or native gardens or courtyards. So these protected areas or natural habitats might serve some habitat restoration for smaller species, but clearly not for larger species. So another option might be something bigger, like a national park or wildlife refuge or a national forest. These are much bigger scale protected areas that we plan for. However, when we start thinking of these large species, like the grizzly bear on the left, or this is our Florida panther on the right, these case strategists, which are sometimes endangered, are large species, really big home ranges. And so buying and obtaining all of that land that they may need for their home range is sometimes not possible, just because it's cost or it's land that is under human development and we just can't get it back. So here's another example looking at a wolf in its home range.
Conservationists elsewhere, such as in the Rocky Mountains, we're also discovering just how much area some animals need.
So we had this wolf called Fluid Wolf. She started just below Banff National Park, and she moved 100,000 square kilometers. She moved across 2 provinces, 3 states, 30 different jurisdictions. It was that kind of movement of animals that caused conservationists and scientists to go, wow, we're not really thinking at the right scale.
Biologists realized that even national parks might not be big enough to support species with large home ranges.
Wildlife, particularly bigger animals, they need room to roam. Well, they can't do that if there's too many human activities and if they don't have the ability to move through that sea of humanity.
So there's a problem. Not only are they losing their habitat, but what they have left is fragmented and they may not be able to successfully navigate those spaces in between. So one solution is something called a habitat corridor. So let's go back to our idea of the grizzly. So we've got lots of populations of grizzlies that are kind of separated from each other. And because of habitat loss and fragmentation, they have, just in general less habitat, but what they have is fragmented. And that results in smaller isolated populations. And we have a limited amount of gene flow here. The genetic biodiversity is lessened simply because of this habitat fragmentation. So one solution, if we cannot get all the land we need because of its use, maybe there's a mine there or it's a farm or we just can't afford it, one possible way is to connect those existing fragments with corridors, smaller patches of habitat that connects those fragmented parts. So here's a quick diagram. If you notice here on the left-hand side, this has 2 clear fragmented habitats. And perhaps they're so far away or there's something in the middle that individuals of this population in the top cannot reach the ones at the bottom. So we're limiting the gene flow between these 2 separated populations. So what I could do in an ideal sense over here on the right-hand side is buy up all this land in between and connect the 2 habitats, the 2 fragments. Or if I can't do that, maybe I can find some little patchy islands. So going back to our example of our indigo snake, ideally it would be nice if I could connect these patches, but perhaps all I can do is afford a few isolated patches so that as they do try to transport themselves between 2 fragmented habitats, they're a little bit more successful maybe. These are called habitat corridors. So let's take a look at them in use here.
But if protected areas are hemmed in, how can you make them any bigger?
I work for an organization that's called the Yellowstone to Yukon Conservation Initiative. It was founded in 1993 with a vision of connecting and protecting habitat from down in Wyoming all the way to the Arctic Circle in the Yukon, a 3,200 kilometer stretch of land.
One way Y2Y reconnects existing protected habitats is by purchasing land to create a wildlife corridor, a larger continuous wilderness through which animals can move.
Our challenge, in order to conserve these species over the long term, is to make sure that we resolve those potentially fragmenting areas and try and reconnect them and keep them connected.
Another important way to link habitats is taking place on indigenous land in western Montana.
We're
here at the south end of the Flathead Indian Reservation. This is the area where Highway 93 cuts through a really continuous block of forested area. Highway 93 is a pretty big barrier with a lot of traffic, and so previously animals had to try to run across this highway.
The Confederated Salish and Kootenai tribes, with the wildlife biologists here, successfully lobbied for the construction of bridges and passages to connect habitats severed on Highway 93.
We're in a really unique area because we have the overpass over here that allows animals to walk over the highway, and then we also have associated underpasses here that let species walk under. Now that we've come into the underpass, the sound is different. The traffic volume is kind of loud, but when you get in here, it's muffled, it's not as loud. You can hear the creek running through the middle, it sounds more natural. In the middle of the summer, wildlife will just lay in these things for hours. They'll be drinking water, they'll just be resting. They can see things coming toward them, so they have some ability to see predators approaching, and it's just kind of cozy for an animal. A crossing structure like this makes a connection between those two patches of land so that animals can move through. It essentially makes them one big area.
Tracking which animals use them is a measure of the project's success.
I'm setting up one of our wildlife trail cameras on the overpass. These cameras are great and they're really useful because they pick up motion. That's what sets them off and sets them to take photos.
So just think here, remember that one of the parts of identifying and justifying a solution is to perhaps collect data to justify that solution. So these camera traps are serving as a way for her to identify the success of corridors they constructed.
We get mountain lions walking through the structure, black bear, bobcats, white-tailed deer.
In the Waidawai region today, we have at least 106 wildlife crossing structures, overpasses and underpasses that are dedicated for wildlife. It's one of the most robust crossing systems in any landscape in the world.
Because of the efforts of communities living alongside the wildlife, the species in this region have the room to roam.
Wildlife moving across the landscape has a cultural value. That we care the wildlife that we're connected to as a tribal people safely flow across the landscape. That we think about their energy, their species, their young being able to disperse all over. So this was really a mix of science, politics, and tribal culture values that made what we have here so special and so important to our people.
So cool. I love that clip. And it just brings to the forefront the cultural impact of some of these ecosystem services. So again, this is really looking at habitat corridors on two scales. On a large scale, it's acquiring pieces of land that can connect very distant fragments with each other, or something on a small scale like these under or over roadway structures. Here you can see one in Africa for elephants. And then education. Education is another huge solution. If you're asked on an FRQ to describe solutions to problems, sometimes education might be an appropriate answer, especially if it's something that could be affected by people buying into it and changing their behaviors. But clearly, as in the clip we just saw, there was some cultural value to that solution as well. So overall, the solution is habitat, habitat, habitat. So if we're trying to conserve a species to protect biodiversity, protecting habitat is a great place to start. And ideally, you want to save or restore large, intact, unfragmented habitats. But if you can't do that, maybe you focus on doing habitat corridors. In terms of conserving habitat, which species you pick might be important. So if you pick these large species like an elephant or a grizzly bear, kind of sometimes call these umbrella species, because if you save the elephant, you also, or if you save the habitat of the elephant, you also save or are likely to save the habitat of many smaller species. Same with the grizzly bear. So again, you should be able to see how what we've just done was a problem, a potential solution, and then we made a claim in terms of those habitat corridors, and we could justify that claim. And really, we could see that the example in the video of how she collected data to support and justify that solution. It wasn't just a habitat corridor for the sake of habitat corridor. There's environmental science behind it as well. So if we circle back to our original question, what could we do to ensure a healthy grizzly bear population? Hopefully, you'll see some ideas there that we talked about. So let's do a quick check for understanding with a couple of multiple choice questions. So the first one says, a large forested area is fragmented into small forest tracts separated by agricultural areas. This change will most likely lead to hopefully pick E, a decrease in the gene flow within the species of the original forest. Let's take a look at another one. Which of the following best describes the disadvantage of creating a series of protected habitats in an effort to maintain biodiversity in an area? So another 30 seconds here. And the answer here would be D. Protected habitats often separate species inside the habitat from other populations of the same species outside the habitat. So being able to talk about pros and cons, advantages and disadvantages, or unintended consequences of solutions. So quick debrief. Did we get where we wanted to go? We briefly talked about biodiversity just as a reminder of what it is. We talked about habitat fragmentation, why that's an important problem to solve, and then some ways to deal with that problem. So this is the question that I'm going to leave you for tonight to go over tomorrow. So this one again is going to ask you to focus on 3 different task verbs. It's going to have you identifying something, explaining something, and proposing a solution. So here's the question. It says biological diversity or biodiversity has become a topic of great concern among conservationists. Biodiversity is often used by scientists and policymakers to help determine the health of ecosystems. So part A starts off by asking you to describe 2 characteristics shared by ecosystems that have high biodiversity. But the 2 parts that I want you to focus on for tomorrow are B and C. B says identify 2 specific human activities that result in a loss of biodiversity and explain how each activity lowers biodiversity. So identify and explain for 2 different human activities. Then let's look at a solution. So for each of the activity you discussed in B, propose a practical solution or practical strategy other than simply banning the activity to reduce the loss of biodiversity. So again, pay attention to your keywords or your task verbs, and pay attention to also the word practical. I know I've mentioned this before that sometimes students will identify strategies that simply are not practical in nature. So try to find something that is. And tomorrow we will go over the answer to these. But before I leave you, just a reminder, if you do have access problems in terms of internet or devices or just connectivity in general, or if you know someone who is having those issues, please reach out to the College Board at the URL below, because that is an issue we need to get resolved as much as possible. So thanks for watching, APES. Have a wonderful night, and I will see you tomorrow. Hello, AP Environmental Science students. My name is Dr. Sowell, and we are going to jump into the review section. So far, Ms. Fassler and I have been going over new content from Unit 8 and 9, and now we are going to go back to Unit 1 and start reviewing the rest of the course. So my job today is to start tackling some of that Unit 1 stuff. Just as a quick reminder, here's the information about our exam date on May 18th, and a quick reminder again that we have 2 FRQs, 60% of which will be the Design and Investigation FRQ, which will ask you to do these types of skills, and then 40% is going to be the Propose a Solution FRQ, which will ask for these skills. So just as a warm-up, let's kind of review what we did last time. So last time we looked at human impacts on biodiversity, and particularly we looked at HIPCO, and we went through each of those letters to talk about how humans have had an impact on biodiversity, but we spent quite a bit of time on habitat loss fragmentation, protected area planning, and habitat corridors. So for homework, I left you with this part of the 2013 FRQ question number 4. So B said, identify 2 specific activities that result in a loss of biodiversity and explain how each one does lower it. And then C asks you to propose a strategy for each one of those 2 things. So let's look at the answers in terms of what's on the scoring guidelines. So you could have said something like clearing land for homes or constructions or for logging. All of that is just going to reduce habitat or fragment habitat. Agriculture is going to do the same thing, but it also has implications for genetic variation. Domestication typically leads to less genetic variation, so things like monocultures. Overfishing, overhunting, overpoaching, reducing species, especially endangered ones. Water contamination, nutrient depletion or nutrient pollution, dropping the DO, the dissolved oxygen. Burning fossil fuels, there's always a good culprit to blame. And so we can look at how that's causing climate change or even issues of acid rain. Then we got invasive species. We talked about that with Ms. Fassler the other day and how that might displace native species. Dams, we mentioned this yesterday actually about how dams could fragment habitats. And finally, surface mining and how that could destroy habitats. So there's a lot of things that you could have answered, but it had to be structured in this way. The activity has to be identified, and then you have to explain how each activity lowers biodiversity. So let's take a look at a student sample here. So this one says, cutting down forests to build homes causes loss of habitats for species to live, so they are forced to migrate. Well, there's points right there. Cutting down forest, there's the activity. What is the explanation of why it causes loss of habitats? So there's 2 points right there. The second part says hunting can lower biodiversity because it can lower populations to a point where they can repopulate quickly enough and they go extinct. So there again, we get hunting as the activity and how that could drive an endangered species to extinction. So this student would have gotten all 4 points for this answer. So you'll remember that the next question says, take these 2 things now and talk about some solutions to each one. So here are some possibilities. So for the clearing land for agriculture or logging, you could do smart growth, compact development, kind of smart city planning, or you could just replant trees or do selective cutting. Agriculture, you can look at issues of polyculture or using IPM, integrated pest management. Overfishing or overhunting, we could look at CITES, the International Ban on Trading of Endangered Species, or our national law here in the United States, the ESA, the Endangered Species Act. Water contamination, you could look at regulations on those point sources of water pollution, or you could look at wastewater treatment facilities as a solution. Climate change, looking at all the carbon sequestration issues, carbon cap and trade, switching to renewable energy sources, and then clearly for acid rain, stick a scrubber on the smokestack, reduces some of that SOx getting into the air. Invasive species, you can kind of check those, tighter enforcement of what's coming in, and then education, always a great solution. Dams, put in fish ladders, salmon ladders that allow the fish to migrate past the dam. And then for surface mine, you can enforce the Surface Mine Control and Reclamation Act, SMCRA. But that's probably not one that we'll focus on today too much. So let's see what this person wrote. Remember, their 2 original things was cutting down trees and hunting. So they start off by saying ecosystems that are very highly diverse should be protected and turned into wildlife refuges and parks so they can't get torn down or changed by humans in a negative way. So let's stop there for a minute. Nothing that they say is really wrong. Those are actually nice ideas, but it doesn't address the issue of logging or cutting down trees. In order to get those points, we would have had to say what's the solution here. The second part says hunt during certain times when the animals aren't breeding so they can reproduce to repopulate the animals killed and they won't be overhunted. Here we get the point for talking about how to regulate that hunting. So the person gets 1 point out of 2 because they didn't do art on trees. Okay. All right, so again, this pattern is something Ms. Fassler and I are going to go back and forth on every other day. So I'll leave you today with an FRQ chunk to work on and she'll go over the answer tomorrow. All right, so let's see where we're going to go today. This is kind of our content goal. We're going to look at 1.1, which is Introduction to Ecosystems, 1.8, Primary Productivity, 1.9, Trophic Levels, 1.10, Energy Flow in the 10% Rule, and finally 1.11, Food Chains, Food Webs. Now, that's a lot. There's a lot of topics in what I'm going to cover in a short period of time today. My thoughts are some of this content is probably things that you remember from biology or maybe even middle school sciences or other life science courses. So this isn't a time to really go into super depth. And plus you've already learned this stuff once already. So this is just going to be a quick review of the basics. And then I'm going to try to find a few points throughout these units to go, okay, let's stop and use it. Because that's what the FRQs are going to ask us to do. It's not going to say, just give me a quick little piece of information. It's going to ask you to identify and describe and explain and justify all those tasks first. So we'll try to find some time to do that today. And then particularly we're going to focus on environmental solutions. So proposing and justifying solutions to problems. All right. So when we look at that practice, remember, it does go from more simple to more complex, all the way from what's the problem, what are the potential solutions, evaluating those solutions with data and evidence, and then making a justification and a claim for which one to use. So here we go. This is 1.1. So by the end of this section, you should be able to explain the availability of resources, or explain how the availability of resources influence species interactions. Let's pause and just kind of deconstruct that a little bit. So availability of resources, species interactions. What this is getting at is that the way species interact with each other is dependent on the availability of resources that they need, and certain resources in particular, things like limiting factors and limited resources. So we'll look at that a little bit more. So to get there, we're going to start by looking at predator-prey relationship. We'll look at how limited resources affects competition, and then we'll look at a specific phenomenon called resource partitioning, and then finally we'll end with symbiosis. All right, so let's eat some stuff. So here's a picture of an egret eating a fish. So in a predator-prey relationship, the predator is the organism that eats another organism, which is the prey. We represent this in food webs and food chains by using the arrow. And remember that the arrow represents the flow of energy from one organism to the next. A common misconception is for students to write the arrow the wrong way. But remember, the arrow shows where the energy is going, where the nutrients going from one organism to the next during predation. So now let's kind of look at competition. So we've got a little lizard here chowing down on a grasshopper, and that will be represented by our grasshopper arrow lizard. But what happens if there's another lizard of that same species nearby? They're starting to compete for the same food resource. And if we throw in another one of the same species, now we've got a lot of members of the same population competing for a food source. So what competition is, it's about limited resources. These lizards are not competing for oxygen. They all need oxygen, yes, but oxygen is not a limited resource. There's plenty of abundance of it. So these lizards are not evolving mechanisms to help them better compete for oxygen. What they're doing is evolving better strategies to compete for something like food. So we can have competition within species. So this green anole, this green anole, this green anole, same species, and they're all competing for the same thing. Or we can have competition between species. So here's our green anole. We've also got a couple of brown anoles, this trunk anole, Anola cybotes. So now we have a bunch of different species of anoles all competing for the same resource. And so what this kind of points us to is that competition for limited resources between species is stronger when species have similar niches. So let me say that again. If a bunch of species, like these 4 species of lizard, have similar niches, similar ways in which they use the resources around them, then that means the competition is going to be stronger. So let's do a non-example. A whale and a zebra. Their niches have hardly any overlap. They do not compete really at all with each other for any kind of limited resource. But there are certain species, like these lizards, who live in the same area who do. So the question that becomes, how are these guys all existing in the same location? Why aren't they out competing each other and driving some to extinction with only 1 or 2 left? Because this is what we saw with invasive species. So if you remember back when we talked about lionfish, these lionfish are invasive species here off the coast of Florida, the coast of the southeastern United States. And what we see is these invasive lionfish have a similar niche to these other larger fish. So their niches are very similar, just like those lizards were back here. So these lizards have similar niches. So do we have it here. But in this situation, the lionfish has just been introduced into this environment very quickly, and it's become an invasive species. And so it outcompetes these native fish for food. That's called competitive exclusion. The competition, it's winning the game, and it's excluding these members that were there before it. So the native population of the fish goes down, and the overall biodiversity goes down. So the question remains, why doesn't this situation where one species dominates over the others, why doesn't that happen in nature? In nature, if you go into the forests of the Dominican Republic, for example, you might find 7 or 8 different anoles living in the exact same place at the exact same time, eating the exact same thing, seemingly. So how are they coexisting? And that's a question we're going to dive into here. So the answer really is something called resource partitioning. Sometimes you'll hear it referred to as niche partitioning, but for the purposes here, we'll say resource partitioning. And it's a way in which using the different resources in different ways or places or at times can reduce the negative impact of competition. So resource partitioning reduces competition and therefore promotes biodiversity. Remember, a healthy ecosystem and a stable ecosystem has high species richness and lots of different species in the one community. So what we want is we want competition to not be strong enough that it drives that biodiversity away. So what we can do is we can see organisms start to share resources in different ways. So for example, if we go and look at the steam bobby kudu and the giraffe, all three of these organisms are eating from this tree, but they're eating at different heights of the tree. So they have partitioned this resource so that they can coexist. Same thing happens with the zebra and the wildebeest, for example. But this time, instead of a spatial separation, they're doing it temporally over time. So that we see while the zebra and the wildebeest eat the exact same species of grass, one's doing it a little bit earlier and one's doing it a little bit later. So you can have species resource partition by space or by time, or maybe even by what they eat. Here's another example, is a famous example of warblers in trees. So we have 1, 2, 3, 4, 5 different species of warblers all coexisting in the same tree because they utilize different locations within the tree. So we're going to take a look at Dr. Rob Pringle's work in Gorongosa National Park in Mozambique. So to give you a little bit of background, Gorongosa National Park currently does not have the biodiversity that it used to have and the species richness that it used to have because of a civil war many decades ago when many of the large organisms were killed or used as bushmeat during the Civil War. But now that the Civil War is over, Dr. Pringle and the rest of the scientists there are trying to rebuild the biodiversity of the park. And so if we think about all those lizards living together harmoniously because of resource partitioning, but then that lionfish problem where they didn't live together because it happened so quickly, what he's trying to figure out is how do they rebuild the biodiversity of this park in the best way possible. And then to do that, he has to understand how all of those different herbivores resource partition. So here's him talking about the issue.
African savannas are famous for their diversity of large mammals. But how do so many similar species coexist in the same place? Princeton University biologist Rob Pringle is captivated by this question, one of the enduring mysteries of ecology. His team is working in Mozambique's Gorongosa National Park. Their focus is 3 closely related species of antelope: bushbuck, yalva, and kudu.
So if we just kind of pause and think about that so far, they just pointed out 3 different species of herbivores, and these 3 species of herbivores therefore have a very overlapped set of niches. Their niches overlap quite a bit. So he needs to understand how they partition the resources so that they can coexist.
They all occur here in the same kind of habitat, and they differ in size. So that enables us to look at how each species is utilizing the habitat, and how do they avoid competing with each other so strongly that they start driving one another extinct.
These species live in savanna, grasslands interspersed with small clumps of trees. At the heart of each clump is a termite mound. Termites concentrate soil nutrients and moisture, enabling the growth of palatable trees and shrubs rarely found elsewhere.
So this is forage that's just incredibly nutritious. I mean, this is cheeseburger, basically.
Ecological theory predicts that to coexist, each species must occupy a unique niche, defined by the combination of habitats and foods it uses.
So we kind of defined the issue here. And so what he did is he went into the field and tracked down different members of these 3 species, and then took dung samples and analyzed the DNA inside their dung to figure out what plants in particular they were eating. I mean, if you look at these 3 organisms from a distance with 7 binoculars, they're all bending down, grazing on what looks like grass. But he had a hypothesis that perhaps they were eating different things on the ground. Well, the only way to really tell that is to do a DNA analysis of their dung to see what they were eating. So here's what he found out.
What our DNA metabarcoding studies have revealed is this really interesting picture of how animals partition the niche.
Each species uses the habitat differently and feeds on a different combination of plant species in varying proportions. Such niche partitioning reduces the strength of competition, preventing a single species from monopolizing all of the resources. In this way, all 3 species can coexist.
So what we're finding is that plant diversity may be really important in helping to maintain large mammal diversity. The presence of termite mounds is actually increasing what might otherwise be a fairly monotonous, homogeneous landscape and adding more diversity to it.
The Pringle Lab's work is revealing how food webs are organized and biodiversity maintained, and it reminds us that ecological communities are profoundly interconnected.
So what we saw there was, over time, over evolutionary time, these 3 organisms have evolved to separate their resources or their niche in unique ways. Why did that happen with the lionfish? Because it happened so quickly. That was an invasive species that we introduced into that system, and there hasn't been time for those organisms to partition the resources, and therefore we see the lionfish outcompeting some of the native fish. So again, hopefully you're starting to see that the trend here with the practices, we identify the problem, use some scientific data to study it, and then to propose a particular solution. So thinking about solutions, could you examine a food web in a particular ecosystem and describe the effects of a particular anthropogenic disturbance, like clearcutting? So if you were presented with a food web or a food chain, could you identify some of the negative consequences of a human disruption or anthropogenic disruption? So during those solution finding times, when you're trying to figure out what's the solution, be sure that every time you do so, you identify the pros, the cons, and any possible unintended consequences of that solution. So now we're going to go into the symbiosis part of 1.1, and this says symbiosis is a long-term interaction between 2 species in an ecosystem, and it can be mutualism, commensalism, and parasitism. So as a quick review, here's a good example of mutualism. We talked about this during our coral bleaching discussion. So this is a coral polyp, and inside the tissues of the coral lives a little algae, and so the algae get this great home to live in, and the corals get the products of the photosynthesis. So both species are benefiting from this close relationship. So mutualism. Commensalism, one benefits, the other's not harm. No big one. So think about barnacles on a whale. These barnacles get transported to these plankton-rich environments. They get plenty of food to feed, but the whale, as far as we know, just got stuff on it. It's not really hurting the whale, so it's commensalism. And finally, go parasitism, parasites. So this is an example of a tapeworm. Humans can sometimes get tapeworms. They can infect dogs too. So you may have seen veterinarians give dogs dewormer to try to get rid of those tapeworms. But the tapeworms are the thing that benefit. They're inside the intestine, feeding off the nutrients and stealing that nutrients from the host animal. All right. So at this point, that's kind of 1.1. So you should be able to explain how the availability of resources influences interactions. So look at predator-prey, competition, niche partitioning, or resource partitioning, and symbiosis. All of those are different ways in which organisms or different species interact with each other. So now we're going to jump to 1.8, primary productivity. So at the end of this section, you should be able to explain how solar energy is acquired and then transferred by living organisms. So to get there, we're going to describe what primary productivity is, describe the differences between GPP and NPP, and finally explain how NPP relates to different ecosystems. So these phrases GPP, NPP, I will define in just a second. All right, so let's just define productivity or primary productivity to begin with. This is just how much photosynthesis is going on in an area. So this is the rate. So it is a rate at which solar energy is converted into organic compounds via photosynthesis over a unit of time. And actually has a very specific unit of measurement, or a type of specific unit of measurement, where it's energy per area over time. So you might think that my front yard of a couple square meters, that is going to have a lower productivity rate than maybe a giant forest because there's more plants doing more photosynthesis, and so the rate is a little bit different. So just think of productivity as how much photosynthesis or the rate of photosynthesis is going on. And also think about productivity as a battery. I always think of productivity or the amount of photosynthesis as the battery battery that drives everything else in that food web. It's the source of everything. Now, obviously, it originates from the sun, but the plants are the things that turn that sunlight into organic compounds that then can be transported throughout the ecosystem. And so keeping that in mind, think about how the productivity in a desert and the productivity of a tropical rainforest might influence the biodiversity or species richness in those two locations. So there is a connection between productivity and overall biodiversity or species richness. All right, so let's talk about those letters, GPP, NPP. Tad bit confusing. So this is definitely a place I would pause and look at a couple of times. I'm going to try to explain it the best I can, but sometimes it's good to hear other people. So Google some other folks. So let's start with some sunlight. So the sunlight hits the grass and it makes what we call gross primary productivity. This is all the products of photosynthesis, all that organic compound that the grass has produced. That's everything. That's what the word gross means. So gross means everything. Now, the vast majority of that is used back by the plant for its own cellular respiration. So that energy, or that energy from the sun through GPP, a lot of it is lost through cellular respiration. Okay? What's left over is NPP, the net primary productivity. That's smaller. And that amount of organic material, organic compounds can be turned into tissues for the plant for it to grow and get bigger. So again, all the sunlight hits all the grass and it makes gross primary productivity, all of the energy, all of the organic compounds. But a lot of that is lost to cellular respiration just by the plant undergoing cellular respiration. What's left over is the NPP. Now, why do we care about the NPP? That's what drives the rest of the food web. So gross, we lose a lot of that to cellular respiration. What's left over is net, and the net primary productivity, or NPP, is what can be passed on through the food web. So just remember this formula that NPP is GPP minus cellular respiration. We, in terms of ecology, are much more interested in NPP because that's what drives the rest of the food web. So again, gross primary productivity is the total rate, and net primary productivity is the rate of energy storage by photosynthesizers in a given area after you subtract the energy lost to respiration. Okay? NPP is the energy that can feed into the rest of the food web. All right, so here's a global map of NPP. So just stare at it for a second, and you might start to see some trends. We get some darker regions in the equatorial region. We see the Sahara Desert have very white, so very low NPP, and that should make some sense to you that not all ecosystems are going to have the same NPP. And in fact, if we look at a chart of ecosystems versus NPP, we can look down here at extreme desert, very low NPP. And then if we go way up here to swamps and marshes and tropical rainforests, very high NPP. So if we know that the amount of energy in NPP drives the ecosystem, we should be able to make some inferences about what kind of species richness and biodiversity we might find there. So you should now be able to explain how solar energy is wired and transferred by living organisms. From the sun, GPP, lose some as respiration, what's left over is NPP, feeds the web. All right, so let's talk about that web. So food chains and food webs, you should be able to describe them and their constituent members by trophic level. So we've gotten energy from the sun into the plant and transferred to those first organisms. But now what? Where do we go from there? We got a deer, we got a rabbit, we got a grasshopper, we got a caterpillar. What's next? And that's good old food chains, food webs. So let's just start this one out. So we got plants consumed by the little mouse is consumed by the snake is consumed by the owl. So here we have a food chain. This is a direct linear relationship between predator and prey. But once we start adding some more onto there, we start to see that our chain really becomes a web. And so that's the difference between food chain and food web. And remember, those arrows represent the flow of energy from one organism to the next. And then we got how if you remove a certain species or certain organism from a food web, how does that change the other members of that food web in positive or negative ways? So for example, let's get rid of the grasshopper. Let's say that someone sprays some really heavy insecticide and kills off some of the grasshoppers. Well, what's that going to do to other organisms? Well, first of all, it's probably going to drop the population of frogs because frogs were relying on grasshoppers as a main part of their food source. So the population of frogs is going to go down. But the population of grass might go up because one of the predators of grass is now gone. And that might in turn increase the population of mice because their food resources are more because they're no longer competing with the grasshopper. In terms of what happens to the other ones, it's a little more unclear because if we look at this snake, one of its prey has gone down and one of its prey has gone up. So as we go a little bit farther up, we have to learn a little bit more to decipher those. So when we talk about disturbances like adding an invasive species or poaching or logging, any of those things, you should be able to look at a food web, find a disturbance, and talk about how that disturbance might affect other members of the food web. So then we have this idea of trophic levels. So the first trophic level is the producers, the primary producers. These are the plants that are undergoing photosynthesis. The next category of organisms are the primary consumers. The primary consumers are the ones that eat the producers. And then no surprise, we've got secondary consumers and tertiary consumers. Sometimes you will have quaternary consumers if we had an alligator in here to eat the heron. But these are the trophic levels that you'll need to be able to describe. So can we do this now? Can we describe food chains and food webs and their constituent members by trophic level? Okay, so hopefully you should be able to do that by now. All right. So if we look at 1.9 says in terrestrial and near surface marine communities, energy flows from the sun to the producers at the lowest trophic levels and then moves up. So that should be no surprise that the energy comes into the lower levels and moves up. But at the same time, we also have decomposition going on. These living things are decomposing and producing waste, and that connects the biosphere with the rest of the biogeochemical cycle. So the nitrogen cycle, the carbon cycle, the sulfur cycle, the phosphorus cycle, the water cycle. All of those biogeochemical cycles are connected to trophic levels through decomposition and waste. We can look at the carbon cycle itself, going from atmospheric carbon into tissues of plants dying and decomposing, maybe compressed into sedimentary rock. So we can see that the food webs are clearly involved in all the biogeochemical cycles. But let's take a look at this question here for a second. Why in the world is this shaped like a pyramid and not a rectangle? Why do we have more stuff here at the bottom than we do at the top? Why are there more primary producers than there are tertiary consumers? Well, that has to do with the energy that's going on here. So we have something called the 10% rule, and that helps us understand the fact that energy decreases as it flows through an ecosystem. So every time an organism eats another organism, that energy moves up, but we lose some of that energy from heat due to the second law of thermodynamics. So what we have is we have a little rule called the 10% rule, which approximates that in the transfer of energy from one trophic level to the next, only about 10% of that energy is passed on. Now, that 10%, that number is an average. Sometimes it's lower than that, sometimes it's higher than that, but the 10% rule gives us a nice guideline to understand it. So what that means is between the primary producers and the primary consumers, only about 10% of that energy makes it up here. That's why this is shaped like a pyramid, because we're losing a lot of that energy. And then again, only another 10, and then another 10. So every time we make a leap, only 10% goes to the next highest trophic level. So if we quantify that, if we want to put some numbers onto it, we can say that there's 3,500,000 kilocalories going on in the producers in this particular community, wherever this is. And then if we look at the next trophic level, the primary consumers, it's only going to have 350,000 kilocalories. And then that goes down to 35,000, and that goes down to 3,500. So we're losing energy as we go down, or as we go up. So this is really having to do with the first law of thermodynamics and the second law of thermodynamics, mainly the second one, because the second law says every time the energy is transformed from one form to another, we lose some of that energy from heat. Again, now we should be able to figure out why it's not shaped like a rectangle, it's more like a pyramid because of that 10% rule. All right, so let's do some checking for understanding. I'm going to give you 30 seconds to answer this question. Select the choice that best fits each statement. And so the statement says it is exemplified by bees consuming nectar and carrying pollen from one flower to another. So take a few seconds and make your decision. All right, hopefully pick mutualism. So this is a mutualistic relationship, type of symbiosis. Let's go to another example. Moss growing on a tree trunk in a forest. All right, so this would be commensalism. One is benefiting, the other one is no big deal. All right, let's go to this one. Losses of usable energy between successive trophic levels in an ecosystem are best accounted for by which of the following? And we just mentioned this a few minutes ago. So this is the second law of thermodynamics. That first law says that we can't create or destroy energy. The second one says that every time we transfer energy from one form to another, we lose some as heat. This is an interesting question. Of the following organisms, which occupies the lowest trophic level? So hopefully you picked deer. I know that sometimes my students will really focus, get caught up on spider here because it's so small and tiny. But remember, the spider is eating other animals as opposed to the deer, which is eating the plant. So the deer is the primary consumer, lower than the spider on the trophic pyramid. All right, let's kind of see where we went today. So we started about how those resources, whether they're limited or not, really affects how species interact with each other. Then we jumped into primary productivity, NPP, and what it really means. Trophic levels, the trophic pyramid, and how that energy flow happens within that pyramid. And then we looked at food chains and food webs. There's a lot that I talked very quickly about. So here is your homework practice for tomorrow. So again, pay attention to the task verbs. These task verbs mean something, and they tell you what types of writing you should be doing in your answer. So this is the Arctic food web question from a few years ago. So the first thing that you should notice here is this visual representation, this model of a food web. You should start looking at the direction of the arrows. You should start looking at who eats who, because the first question says, refer to the food web above to complete the following table. So identify primary producer, identify primary consumer, and identify secondary consumer. So take 30 seconds and answer those three real quick. All right, so you should have said primary producer is the diatom, this phytoplankton down here, and the primary consumer is the krill, the zooplankton. And then for secondary consumer, you could have said either the cod or the seal because they're both secondary consumers. B says, other than showing which organisms are consumed by other organisms, describe what is indicated by the direction of the arrows in the diagram. And I said it a few times today, but you should remember that those arrows show the flow of energy among trophic levels. It's showing the direction of energy flow from one organism to the next. So this is the part that I would like you to do for homework. So this is part, well, let me go and read the top part. It says, as the amount of sea ice has decreased, larger expanses of the Arctic Ocean are now completely free of sea ice for several weeks each summer. Ringed seals, the preferred prey of polar bears, comes to holes in the sea ice to breathe. So C and D asks you about this problem and why that's affecting polar bears' ability to hunt and feed, and how there's a feedback loop with the melting sea ice. What I want you to answer for tomorrow is E. E says many species, including some whales and birds, will travel thousands of kilometers during annual migrations. So EI, provide one reason a species may migrate a long distance. So just one reason. Provide. II says the North Atlantic right whale migrates between subtropical and polar waters annually. Nearly 50% of the right whale deaths are due to human activities. Describe one commercial activity other than whaling that may result in the death of right whales. So we're identifying a problem here. Now let's do a solution. EIII says describe one strategy that could reasonably be implemented to decrease right whale deaths caused by the commercial activity you described in part II. I'll focus your attention again on the word reasonably. We've talked about solutions before. Just be sure that your solutions that you are proposing are practical, realistic, reasonable. So just one more quick reminder. We know that connectivity might be an issue for some students. So we're working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity or know someone who does, you can reach us at the URL below. So thank you for watching. I was glad to virtually see you today. And tomorrow Ms. Fassler will be here and she will start you off by answering the question about the Arctic food web that I let you with. All right, have a good rest of the day.
Hi students, welcome back to our virtual classroom. You got to spend some time with Dr. Sowell yesterday. We're transitioning from covering that new material in units 8 and 9 to starting in on the actual review. So welcome from Marshfield, Wisconsin. I know that all of your teachers are missing you. I'm missing my students as well. But Dr. Sowell and I are so glad that you're spending some time being our virtual students. And so we're going to take just a minute and look at this slide that you've seen a couple times already, and I'm probably going to see a couple of more times to remind you the date of your national exam, Monday, May 18th, and that you're going to write 2 FRQ questions. One of them is focused on designing an investigation. The other on proposing a solution. And remember, the first 2 bulleted points here are the same. And then today we're going to spend a little bit more time kind of in the design and investigation part of it, at least for the homework that you do. So let's take a minute to warm up. Yesterday with Dr. Sowell, we introduced or got started in the review in Unit 1, and I'm going to cover kind of the targets in the middle section of Unit 1 today. I think that as we go through this information, you're going to see that it was really helpful to go back and spend some time learning that content in important Units 8 and 9 so we can make some connections. The model that Dr. Sowell introduced yesterday, where he reviewed some content, we did a little bit of practice together, and then he left you with a part of an FRQ prompt that you could write on your own so that you really get time to practice that. That's the model that will carry through for all of the additional review lessons. There are 18 of them all together. So let's take a look at the homework that you did. You can grab that, the assignment that you wrote yesterday. You spent some time yesterday looking at ecosystems, and you looked at that cool Arctic food web, and the prompts that you did for homework were having to do with why animals migrate. That's kind of a new learning target for us in our somewhat adjusted curriculum this year. So in taking a look at letter E, many species, including whales and birds, will travel thousands of kilometers during annual migrations. Provide one reason for that a species may migrate a long distance. So you can check your answer and see if you would have earned the 1 point for this. I think most of my students probably went with this first bulleted point, that animals migrate for their source of food or a source of water. The next bullet, maybe the food that they eat migrates. So a whale might follow a school of fish that is migrating. I think probably the next most used answer had something to do with migrating for availability of breeding grounds or nesting grounds or areas or protection from predators to rear their young. So hopefully you earned that point. Let's take a look at a sample student response to give you a little practice on if you can pick out if an answer does correctly qualify for earning a point. So take just a couple of seconds and read that response and see if you point it or not. And obviously this student earned that 1 point. They talked about seasonal temperature changes, and that would coincide with this third bullet, more hospitable climate during certain seasons. And just remember that whenever you see that provide a reason, a nice prompt, a nice term to get you prompted to move in that direction is simply to say, well, they do this because I'm providing a reason for that. Letters II and III that you answered to describe one commercial fishing activity other than whaling that results in the death of right whales, and then that was worth 1 point. And then the next one, describe a strategy that would be a solution to that problem or could mitigate that problem. I will point out that it's really important that you read all of the prompt. Notice in the first part of that prompt, and I always tell my students before starting to write any part of their FRQ, read the entire thing all the way through first and just take a minute to sit back and process kind of where that question's going. Notice that if I had read II before I read I, it kind of gave me a lot of information here. They tell me that whales migrate between subtropical and polar regions annually. So right there, I kind of got, oh, they're moving to a different climate. So the one thing I want to point out as you start to grade this is that they are 1 point for each answer, and that the strategy, the activities and strategy are linked. In other words, if I did not provide a correct commercial activity that threatens whales, I could not earn a point for a strategy. So that's not super common that points are linked, but it may occur on one of the questions that you see. So I think the most used response, a commercial activity that threatens whales, is that they get caught in, they end up as bycatch. They get caught in fishing nets or fishing gear from other fishing activities. Oftentimes the ships, large commercial transport vessels, are the channels that those ships use are the same as the migration lane for the whales. So that could be a commercial activity. And then some form of noise pollution that can disrupt a whale's navigation system. As we look at a solution or a strategy to mitigate that, what I want to point out is you want to avoid saying, oh, well, just don't let fishermen fish anymore and there won't be any bycatch if we don't let them put nets out there. Rarely can we have a justifiable, reasonable solution simply banning or eliminating a process. So if you're a little bit unsure, always think if you can express a way that you can reduce the impact of something or limiting it or providing an alternative. And notice that that idea comes up in a lot of our descriptions of strategies. Changing a type of fishing method. When I fish, the time of year that I fish, maybe I don't get to be in that fishing area where whales are migrating. A reduction in seismic survey activity. Again, maybe even particularly when whales are migrating. Installing quieter motors. And then we certainly have this general idea that I can often regulate. A solution is to find people who don't pick up their nets from the ocean and leave them to threat fish populations. So hopefully you got at least one of those points, maybe both of them. I'm going to show you the rest of that student's response. So remember what we're looking for here. Describe a commercial activity that results in the death of whales and a strategy to reduce that. So let's take a look at this student response and see if you would give that 0, 1, or 2 points. And actually, the student earned 0 points for this. They did not earn the point for the activity that threatens the whale population because fishing of other fish does not directly cause the death of right whales. And if they didn't earn that first point, they could earn the point for a solution or strategy to decrease the effect of that. A note on misconceptions that came up when the readers were looking at this exam last year during the grading is that there seemed to be kind of a misconception about why animals migrate. And many students wrote in such a way that they indicated that they felt that animals migrated because of some type of human interaction with the environment or some type of abrupt change in the environment that just randomly all of a sudden caused that animal to migrate, rather than understanding that that's an annual cycle. So we're going to go into the second part of Unit 1 today, and our big theme is biogeochemical cycles. We really spend all of our time today in this big idea of interaction between Earth systems, this little Earth abbreviation. The Earth is one interconnected system, and natural systems change over time and space. Biogeochemical systems vary in their ability to recover from disturbances. So we're going to demonstrate that we understand all of that big idea and can communicate that information by focusing on these two science practices. Visual representations, that both of our FRQs have that bulleted point in them, and obviously if you remember your biogeochemical cycles, we're representing all of them with a model, with a visual model. And then, as I mentioned, we're really going to focus on scientific experimentation primarily in your homework for tonight. So let's start off with our first kind of a general idea about biogeochemical cycles. They describe ways in which chemical elements move between biotic and abiotic components of an ecosystem. And so that's kind of like, how do chemical elements move between the living and the non-living portion? Like elements go from being a rock to being a plant or an animal. The chemical then, when we look at the model of that, it depicts the movement of atoms between sources and sinks for that biogeochemical cycle. They're called cycles because matter is conserved, and biogeochemical cycles facilitate the acquisition and transfer of energy into usable forms. Here's where we're really going to connect what you talked about yesterday with Dr. Sowell, where you looked at the energy transfer from one trophic level to another, and the second law of thermodynamics, that energy sort of peters out by the time I get to that top trophic level because there's a diminishing of energy quality. But in biogeochemical cycles, we keep taking the same atoms and moving them from one place to another and reusing them over and over and over again. And obviously, we'll take a look at ways that humans have disrupted those cycles. That's what you should know by the end of our class period today. What you should be able to do is use those visual representations to describe a process and then predict how, if I have this system that's functioning the way it should, what happens when humans interfere with one part of that system? How does that throw the rest of that cycle out of balance? So let's start by looking at the phosphorus cycle. I keep remembering that this is all review for you, so you've seen this before. And remember, our model is going to be to go through some content and give you a chance to practice practice with the skill set at the end, and then you'll grade that tomorrow with Dr. Sowell. So I'm going to go through these steps rather quickly, and then we'll take a step back, kind of summarize the big idea. So we start out in the phosphorus cycle with rock weathering. This is some type of phosphorus-containing rock, and that rock breaks down and releases that phosphorus into the soil. I'm in the abiotic component of my ecosystem now. The next thing that happens is that plants can take up that phosphorus now that it's in the soil, and they assimilate it. They use that inorganic phosphorus from the non-living component of the environment, and they use it to build plant tissues. Think of like DNA is a biomolecule that has phosphorus in it. Well, then we have this little elk here, so that elk is munching on that plant, and whatever phosphorus compounds were in the plant, the animal has now gotten. See how we're combining that idea of food webs and energy transfer with biogeochemical cycles. That animal is then peeing and pooping, and in that process, that waste gets returned to the soil. And the minute that waste gets returned to the soil, a plant can take it up again. And so this part of the cycle is going pretty quickly, but we have this big issue that limits phosphorus in ecosystems. Some of that phosphorus is going to run off into the ocean and very slowly be incorporated into sedimentary rock, either sediment on the bottom of the ocean or on land. But the big takeaway that you should have from the phosphorus cycle is that it happens really slowly. The major reservoirs of phosphorus are rock and sediment that contain this element phosphorus. And so a lot of the processes that are moving that phosphorus around are happening very slowly. Weathering of rock, geologic uplifting. And the other really big concept, and this will make a lot more sense when we frame it and compare it to the other biogeochemical cycles, is that this is probably one of the big things you remember about phosphorus. There is no atmospheric component. And because phosphorus never exists as a gas in the atmosphere, it doesn't cycle very quickly. And this limits the limitations this imposes on the return of phosphorus from the ocean and the land make phosphorus naturally scarce in aquatic and terrestrial ecosystems. And that is one of the big reasons that we were so excited that you watched our Unit 8 and 9 videos, because this is where we made that connection to that lecture Dr. Sowell did on eutrophication. The humans disrupt the phosphorus cycle because it's such a limiting factor in biological systems, because of that slow breakdown of rock and sedimentary uplift, that we often have to add phosphorus-containing fertilizer to an agricultural field to get a good productivity, a good yield. We even put so much phosphorus on our lawns just to cut them every week and not really harvest any food. Doesn't really make much sense. But a lot of that phosphorus is going to run off into an aquatic ecosystem. It's plant food, just like my plant got and assimilated that phosphorus into organic material. That's plant food for phytoplankton or algae. And when that algae decomposes, they cause a big drop in the amount of oxygen. We get these dead zones, like you can see in the Gulf of Mexico. This is some NASA MODIS satellite imagery that shows me the Gulf of Mexico in the summer and the winter. And the red and orange colors are indicating high concentrations of phytoplankton. The next cycle we're going to look at is the nitrogen cycle. This is one of my favorites. So the big ideas about the nitrogen cycle, let's kind of go through the nitty gritty and then we'll take a step back again. The major reservoir for nitrogen is the atmosphere. 78% of the atmosphere is nitrogen. It's this inorganic, abiotic molecule of nitrogen gas. gas. And the first step in the nitrogen cycle that we need to know about is this step called nitrogen fixation, where I'm taking atoms of molecular nitrogen gas and converting them to ammonia. And by the way, if I'm going to write about or describe this process on an FRQ, I can always put the name of the chemical compound ammonia, or I can put the formula for the chemical compound NH3. And if you remember when you first studied the nitrogen cycle, this seems pretty straightforward when I look at it. But remember, it's not like the carbon cycle where plants have this amazing ability, because they have these chloroplasts, they have this ability to take inorganic carbon dioxide and convert it to a sugar. We'll look at that in a minute. It doesn't work that way with nitrogen. Plants can't just diffuse this nitrogen gas into their leaves and do that conversion. So if you remember, let's take a close-up look here. Oh, that's right. We have these special legumes that have these nodules in their root that have bacteria, and it's these amazing soil microbes that are actually doing this chemical conversion. So not all plants have the ability to take atmospheric nitrogen and convert it into ammonia. That ammonia then, just like that phosphorus, once it got into the soil into a usable form, then the plant took it up. Same thing happens with nitrogen. We've got this pattern emerging that once I get it into the soil into a form that a plant can take up, same thing. That plant's going to take that ammonia and assimilate it into plant tissues, nitrogen-containing plant tissues, like proteins, for example. So now I've got that assimilated into the plant, and then little bunny poo-poo here is eating that plant, and then the bunny poops, and that nitrogen goes into the soil, and soil microbes, those decomposers that in the food chain, break this organic biotic nitrogen down back into an inorganic form so it can be taken up by a plant to be eaten by an animal. So look at the idea here that there's rather rapid cycling for the most part of nitrogen. And we just keep this part of the cycle just keeps going and going and going. So now let's take that step back for a second. In terms of kind of the big takeaway, most of the reservoirs in which nitrogen compounds occur in the nitrogen cycle hold those compounds for a short period of time. Unlike the phosphorus cycle, most of the reservoirs like rocks and sediment hold that phosphorus for a long period of time. But in the nitrogen cycle, that bunny is eating and pooping a couple times a day. So they're holding that nitrogen for short periods of time. Just like phosphate or phosphorus can run off and cause eutrophication, nitrates or nitrogen can do the same thing. And then you may remember from Unit 7 on air pollution, there's a kind of a tough concept on the formation of ground level or tropospheric ozone. We'll review it in Unit 7, but I'll mention it now so we can reconnect in a couple of weeks. When I burn gasoline in my car, the nitrogen impurities in that gasoline are emitted as NOx, that nitrogen oxide compound that is a very harmful gas in and of itself and a precursor or component of photochemical smog. So let's take just a minute to kind of check in a little bit and see how we're doing on interpreting these diagrams so far. So this diagram depicts processes involved in the nitrogen cycle. Remember, even though this, and I kind of reframe this so it's not multiple choice, we're going to have to describe a lot of processes. So this is just really good little checks that we get the content and a little bit of skill practice. Which reservoir contains the majority of nitrogen? And you can't get that by looking at the diagram because I see reservoirs, but they're not quantified for me. So that's just something that I have to know, that the atmosphere of those reservoirs listed all contains a lot of nitrogen. This is something where we need to interpret the diagram directly. And this is something they could ask me in an FRQ prompt. They could present me with a diagram and ask me about a process. So what process is illustrated by the downward arrows from the atmosphere that show the conversion of nitrogen gas into usable forms available by the plant. So get up to these usable forms that are right available for plant. They gave me a big clue here. What we just went over. Remember that step is called nitrogen fixation. They're fixing the nitrogen. We're going to talk about fixing carbon here in a minute. I'm just fixing it or converting it to a form that can be taken up by plants, and plants then assimilate that or use it to build their body tissues. Here's another diagram. Which of the following statements is best supported by the diagram of the phosphorus cycle? I'll give you a minute to look at that one. And obviously the correct answer is that phosphates absorbed by animal tissue eventually, through consumption, eventually return to the soil. You intuitively should have known that based on our review we just did, but certainly the diagram depicts that. Notice there is no atmosphere shown, and that's something we probably remember about the phosphorus cycle. And plants cannot take the phosphorus up from the rock directly. That rock first has to break down or weather. That's why it's so slow. And phosphates are soluble in water because they show me up here in solution. One more, again, kind of more of a higher level application or interpretation of the processes shown in the cycle. We have the phosphorus cycle here again. Farmers in a suburban coastal town started using no-till agriculture, not tilling the soil, a practice that reduces soil erosion from their farmland. Use the image to determine which of the following long-term effects no-till agriculture will have on the ecosystem surrounding the farmland. Reduces erosion. And the correct answer is there will be less algal growth in the nearby ocean. If I don't have erosion, I don't have an increased need for fertilizer. I probably have a decreased need because all that fertilizer is staying on my cropland where I put it. We don't ever have phosphorus in the atmosphere, and this just takes more time. Remember, I'm not going to see a direct impact of that. So let's just make sure we can talk through this process because this is the kind of thing that we might have to do on an FRQ. If I decrease erosion, I decrease runoff. If I decrease runoff, I decrease that nutrient enrichment. I decrease the amount of phosphorus that entered my marine ecosystem, and there I decrease algal blooms. You guys are rocking! We're just sailing through this. Let's go to the carbon cycle. Carbon cycle might be my favorite cycle now that I think of it. So we have a lot going on with the carbon cycle, and we're going to come back to the carbon cycle again and again and again and again as we talk about climate change through the rest of the review sessions. So the kind of big overarching idea they want us to come away with is that some of the reservoirs in which carbon compounds occur hold those compounds for a long period of time. That's kind of this geologic carbon cycle. Then we'll look at the second half of that statement. Some processes or reservoirs in the carbon cycle hold them for really short periods of time. So let's see what's going on here. This is our geologic carbon cycle. I'm representing just very simply the atmosphere, the ocean, and the lithosphere, the rocks, the solid part of our planet. And I started getting that carbon dioxide into the atmosphere to begin with. And because this is a geologic representation of how carbon cycles, this is all the abiotic. I'm not other than this isn't even living though. It's just the shell of an organism. So all I'm doing in this part is the inorganic part of the carbon cycle. I haven't gotten into any of the living things yet. So this is what happens on a planetary evolution scale. We got a trickle slowly. Carbon dioxide came through the venting through volcanism and built up in our atmosphere again from a planetary evolutionary standpoint as our atmosphere was forming just this right concentration of gases. So once that CO2 is in the atmosphere, it can go right into solution and dissolve in ocean water. Or, and you remember this from the air pollution unit, it can form carbonic acid. It can form acid precipitation. So that carbon dioxide combines with water. That acidic or low pH precipitation can now weather rock. And the carbon can enter the ocean through that weathering of rock as well. Once I have this carbon in my ocean water, remember when Dr. Sowell talked talked about coral ocean acidification and looked at the idea of how corals build their shells with that carbon. See how this is all coming together. It's so cool. They can actually take some of that and build carbonate or bicarbonate ions. Don't be concerned if you don't remember the chemical formulas for those. That's kind of a little bit higher level, even knowledge statement. As long as if you can get the idea that dissolved carbon ultimately is going to be used by shell organisms to build their shells. Some students on an FRQ, I think you may have looked at part of it yesterday, were very eloquent in their description of these chemical conversions, but I don't want you to get bogged down in all that detail. Carbon dioxide gets dissolved and shell organisms use it to build their shells. And then just like the phosphorus cycle, we can build that sediment up over time in sedimentary rock. And in the case of carbon, it's stored in fossil fuels in the lithosphere for long periods of time. And then maybe I have subduction. Maybe I have that lithospheric plate subducting and I get that volcanic eruption, that chain of volcanoes that occur along that subduction zone, and I can release that carbon dioxide back to the atmosphere. So all of this is happening on a very slow geologic time scale. Well, let's take a look at the processes that hold carbon in the carbon cycle for relatively short periods of time. And this is where we're really making the connection between what you did yesterday with energy transfer and what we're doing today with matter recycling. So in the process of photosynthesis, and many of you could write and balance this equation, all we really want you to take out of here is what's happening with the carbon. I'm going from an abiotic, inorganic source of carbon, CO2 from the atmosphere, and this miraculous process of photosynthesis converts that into a sugar, a carbohydrate, a food that plant uses. And then remember, just like in the nitrogen and phosphorus cycle, an animal is going to eat that plant and get the sugar, the carbohydrate from that. When the animal eats that plant, it has to break that plant body down. So little bunny foo-foo is eating that plant and it digests the sugars that plant made, and it converts the sugar, the carbohydrate, back into carbon dioxide. And so remember that living things all need energy. So if plants have to do that process of cellular respiration as well, you look at that with the idea of gross and net primary productivity. So to reiterate, we have this rapid cycling of carbon where this plant is all day long when the sun is out. This big tree is photosynthesizing and making sugars, and then those bunnies are coming along and eating the leaves of that and breaking down that sugar and turning it into energy and giving off carbon dioxide back to the atmosphere as a byproduct. So I'm going to show you a quick NASA video, a really cool animation, mostly compiled from satellite imagery that shows me that rapid cycling of carbon, and then we'll take a second to describe what we're seeing in the video.
This is carbon dioxide, or CO2, in the Earth's atmosphere. It is derived from the synthesis of observed and simulated data. Reds and yellows show regions of higher than average CO2, while blues show regions lower than average. The pulsing of the data is caused by the day-night cycle of plant photosynthesis at the ground. As CO2 is lifted away from the surface, it is rapidly spread around the world by high-altitude winds. The high concentrations are from the buildup of CO2 during the northern hemisphere winter, when photosynthesis is not active. By July, photosynthesis in the vast vegetation regions north of the equator draws massive amounts of CO2 out of the atmosphere, resulting in low carbon dioxide across the entire northern hemisphere. The growth and decay of vegetation in northern lands cause the seasonal change in atmospheric carbon dioxide seen here between March and July. While seasonal changes in vegetation growth control CO2 on monthly timescales, human activities govern long-term carbon dioxide trends.
I'm sorry, I'm going to back this up just a little bit so we can see that image. Stop here. So I want to make sure that you understand, I've done a couple of these things before where we indicate a process by showing up and down or increase and decrease arrows. So I know that March isn't winter for some of you, but for those of us in northern latitudes, this is still winter. So a lot of times when students write about this rapid cycling of carbon, it's super easy for them to get this process kind of reversed. So in the northern hemisphere winter, where I have these massive amounts of land plants doing photosynthesis, in winter, they're greatly reduced photosynthesis. Less photosynthesis means higher concentrations of CO2 in the atmosphere because plants aren't removing it. And that's where I see these reds and yellows. And then in the northern hemisphere summer, in July, all of those plants are rapidly converting that carbon dioxide from an inorganic form to those sugars, and the carbon dioxide concentration in the atmosphere goes down. One thing you may have noticed is some kind of big plumes of carbon dioxide in the southern hemisphere, in South America and Africa. We often see that, and NASA is really tracking, especially because of increased fires due to climate change and fires that are set by humans for slash and burn agriculture. We see big plumes of carbon dioxide during fire season. Again, whether those fires are naturally set by humans for clearing land or forest fires that were sparked. So let's take a step back now and kind of put together that geologic and rapid cycling of carbon and make sense of these two big concepts that we want to make sure we understand. So this diagram is showing me pools and exchanges for different amounts of carbon. This GT, this is a gigaton, the unit, the amount of carbon stored there, and that's 1 billion metric tons of carbon. And so a couple of things might surprise you. There's a lot of carbon stored in the ocean. Look at the amount of carbon in the deep ocean. This is an area that climate scientists are really looking at, is how much carbon is being stored in the deep ocean and how temperatures of the deep ocean are changing. Let's see if we can make sense of some of these arrows, because every lettered arrow here is depicting a process. So the first thing I notice is that arrows A and B seem to be complementary, and the amount of flux or the amount of carbon moving from source to sink isn't indicated there, but I will share with you that these amounts are rather, we're kind of in equilibrium. So you should be able to tell me the name of the process that takes carbon out of the atmosphere and moves it into vegetation. Photosynthesis. And then complementary to photosynthesis is cellular respiration, letter B. And those two quantities of fluxes are kind of imbalanced. The amount, if things are normal and humans haven't intervened too much, the amount of CO2 taken out by plants is kind of the same as the amount of CO2 put back in through cellular respiration of living things. Looks like we have some other kind of complementary arrows here. Remember we said that carbon dioxide gas could dissolve in ocean water, and that CO2 gas, just like CO2 can jump out of solution when I open up a can of soda, there's an equilibrium there. That CO2 molecule just went into solution and then came out of solution. But those quantities, those fluxes are kind of the same. What else have we got going on here? This is that arrow that's showing me from like sedimentary or igneous rock. That's that very first slide of the carbon cycle. This is a tiny little trickle. We don't really care about this amount. That's the CO2 that goes to the atmosphere from that geologic, like venting from a volcano. And it's this tiny, tiny, tiny amount that is not increasing the overall amount of CO2 in the atmosphere. What else have we got here? What's this arrow C? That's going from, yes. Carbon can run off from the soil into the upper ocean. I did want to point out that although we have respiration from vegetation returning carbon to the atmosphere, we have this huge amount of carbon stored in soil. That's all those soil microbes that are doing all that decomposing and all of that turnover of carbon from biotic, abiotic, and back and forth. Those soil microbes are living things that need energy and do soil respiration. So that's why part of that arrow B is going back there. The only other thing I have here then is letter H, from fossil fuels to the atmosphere. What I want you to understand is that, again, we don't care about this arrow. Of the arrows that are going to the atmosphere, the fossil fuel arrow has nothing that balances it, that takes that CO2 back out to the atmosphere. Remember that plant and animal decomposition have led to a lot of storage over hundreds of millions of years. This is carbon stored in fossil fuels. The burning of that, the combustion or oxidation of this geologic stored carbon, is rapid rapidly moving carbon dioxide into the atmosphere at an unnatural rate. In fact, one of the latest reports from the International Panel on Climate Change, International Governmental Panel on Climate Change, is showing us that we are adding 38 gigatons of carbon to the atmosphere through the combustion of fossil fuels. Let's do a quick check on the carbon cycle. Which of the following major storage reservoirs of carbon stored in the form of carbon dioxide is not represented on the graph? And I'll give you just a second to look at that. And the obvious one that we don't see here is the ocean, and we just kind of review that. CO2 gas can go into solution and come out of solution. And it's important that when we're talking about carbon being in the atmosphere, if we mean carbon dioxide, we have to say carbon dioxide and not just carbon. If it's atmospheric carbon, call it carbon dioxide. So we have one more cycle to look at, and that's the hydrologic cycle. We're going to focus on the processes and interactions here. So the hydrologic cycle is powered by the sun, and it shows me the movement of water in various solid, liquid, and gaseous phases from sources to sinks. So I have water evaporating from the surface of the ocean, or transpiration, evapotranspiration for plants. That water, as that evaporated water rises, it cools off and it condenses and falls as precipitation. It can percolate or infiltrate through the soil and recharge groundwater. It can run off into surface water and eventually into the ocean. So let's take a look at the hydrologic cycle kind of in action. I've got this cool little animation. We're going back to Africa. We've been there a couple of times to illustrate, to let you see kind of more in action these processes in the water cycle, the hydrologic cycle, and then we're going to make a couple of connections.
Morongosa's water cycle starts with the evaporation of water from the Indian Ocean. The moisture-laden air moves westerly on the trade winds across Mozambique before reaching Mount Morongosa. The elevation of the mountain forces the air to rise, thus cooling it. This then leads to condensation, which results in rainfall. In addition to supporting a lush montane rainforest, the water runs off the mountain to feed the rivers that supply Lake Huron. During the wet season from November to mid-March, there's enough moisture in the air so that clouds form rainfalls throughout March. The lake overflows may cover as much as 200 square kilometers, transforming a dry, grassy plain into an enormous watery haven. But much more rain falls on Mount Morongosa, which also acts as a reservoir by soaking up some of the rain into its soil and releasing it slowly throughout the year. As the rainy season passes and fewer clouds move over the park, the floodplain retreats. Many of the rivers start to dry up. That's when the water captured and released from Mount Morongosa becomes critical. During the dry season, as much as half of the water flow into the park is provided by the mountain.
What a cool visual for us to see kind of in action how the water cycle works. I bet some of those animals migrate for water supply too. I bet they migrate for food or water. So let's see the connection that we want to make here. Climate change is really disrupting the hydrologic cycle. It's intensifying, because if you think of it, if I increase my air temperature, I increase the rate of evaporation, and warm water can hold more water vapor. So it leads to really intense rainfall and intense downpours. We're seeing this, I know, a lot in central Wisconsin, really a disruption to our rain patterns. And even citizens are collecting data to supply scientists by keeping rain gauges in their backyard. It's not necessarily the total amount of rain, it's that rain is coming down really hard, intense rainstorms. Warmer water intensifies hurricanes and severe tropical storms. Warmer climates melt land ice, causing sea levels to rise. So humans have many ways that we are impacting the hydrologic cycle. So we're going to go through a guided practice question that gives you a little bit of a chance to practice some of the content and skills that we've been looking at. Remember these command terms that you're going to see on the exam. And we're going to start off. You can jot your answers down, think about them verbally. I'm going to kind of walk you through this, and then I'll leave you with your homework question to go over with Dr. Sowell tomorrow. The atmosphere is one important carbon reservoir. Describe a biological process by which carbon is removed from the atmosphere and converted into organic molecules. Notice my command term is describing a process. It doesn't ask me to name it. It doesn't say identify the name of this process. It asks me to describe. I also want to describe a biological process in which carbon is converted from an organic molecule and returned to the atmosphere as a gas. And then oceans and terrestrial systems also are important carbon reservoirs. Explain how atmospheric carbon is incorporated into 2 oceanic sinks, and identify one terrestrial sink other than fossil fuels that stores carbon for thousands to millions of years. Let me give you a minute to think about that one, and then we'll check the answers. How are we doing? Let's check. Okay, describe a biological process. And I kind of prompted you there. Notice that no point is given simply for saying photosynthesis without a description. I can say photosynthesis is the process in which, and then there's a number of ways I could have said that. Plants or autotrophs take in, notice they were really explicit here about carbon dioxide from the atmosphere and converted into, there's a lot of different ways I could say that, converted into food or glucose or sugar or carbohydrates, starches. I could also have said that plants or autotrophs fix carbon. I didn't need to necessarily specify carbon dioxide here because I'm not talking about pulling it out of the atmosphere per se. I'm fixing it or converting it into one of those foods or sugars or carbohydrates. Same thing for the next 1 point description. I don't earn a point simply for saying the word cellular respiration. And notice again that the answer must identify a form of carbon being released as part of the description. So I could say in cellular respiration, that's fine. I don't even need to say it. I'm guessing most of you did, but the real key here is describing the process. Organisms, plants, and animals break down food and release carbon dioxide back to the atmosphere. We can have some methane emitted from animals. A lot of cows, for example, will belch or fart methane, depending especially on the diet that they eat, because of the breaking down of the cellulosic material, or the decomposition of organic matter by bacteria. We looked at that in the soil, converts organic carbon into gases such as methane. The next part was to explain how atmospheric carbon is stored in 2 ocean sinks. I hope, and I'm guessing a lot of you talked about the fact that atmospheric CO2 can dissolve directly into ocean water. Plants, aquatic phytoplankton, can remove carbon dioxide and take it up through photosynthesis just like land plants can. Remember, I didn't even need to get specific about the carbonate and bicarbonate. I simply needed to know that that carbon was used for marine organisms to build their shells. And then we have a couple other possible answers that you may have looked at. And finally, one terrestrial sink other than fossil fuels that stores carbon for thousands to millions of years. And this is kind of a tricky one. If you simply said forests store carbon, it would not have earned you a point, because I gotta tell you, we have a school forest and we harvest trees about every 40 years. Obviously, while they're alive, they're storing carbon, but they're not considered long-term carbon sinks. So it would have to be an old growth forest. And many of those forests will store carbon for that long a period of time. Some of you may have gone to that sedimentary rock or limestone incorporated into soil. We saw that was a really big sink when we looked at that diagram. So that should have been a pretty easy 1 point to come up with. And let's take a minute to look back and kind of summarize what we did today and see if we met our objectives. So this was kind of that big takeaway from the phosphorus cycle. Go back and get the big conceptual idea of the geologic processes involved in the phosphorus cycle. But our big takeaway is that there's no atmospheric component, and the limitations this imposes makes it phosphorus a limiting factor in many ecosystems. Most of the reservoirs of the nitrogen cycle hold those nitrogen compounds for a relatively short period of time. There are many ways that humans are disrupting the carbon cycle, and I would really encourage you to go back and look at the lecture in Unit 9 on global climate change if you haven't, it so you can make that bridge and connection. And then we kind of demonstrated that we could demonstrate our understanding of this. We did a lot of looking at visual representations and practicing that explain how atoms are moved from sources to sinks, and looked at and made predictions about changes in a cycle based on human impacts. So I'm going to leave you with an AP exam practice question that you'll go over the answers tomorrow with Dr. Sowell. You are going to be looking at biomes tomorrow, so this will be kind of a nice transition. Let's read through the question and the prompts together. The carbon cycle describes the movement of carbon atoms between sources and sinks. Scientists are concerned about increasing concentrations of carbon dioxide in the atmosphere because of the impacts of global climate change. Sure, I can read this. Soil microbes that decompose soil organic matter play a critical role in carbon cycling and storage by returning carbon dioxide to the atmosphere through the process of cellular respiration. Put that in the soil. Scientists are interested in researching how increasing soil temperatures will affect the rate at which soil microbes decompose organic matter. They design a laboratory experiment in which they measure the change in the amount of CO2 in soils incubated at different temperatures for a period of 5 days. All the soils were collected from the same location. It looks like this is a lot, but they go pretty quickly. Explain how carbon enters the soil. We just practiced that with different sinks and how that moves around. Explain how carbon in the soil is returned to the atmosphere. And then here's our 3 practice prompts on experimental design. Identify the independent variable, identify the experimental control, and describe how the amount of CO2 would change if temperatures got so high that they actually kill the soil microbes. So just a quick, make sure you write that out. You're going to check it with Dr. Sowell tomorrow. Thanks for watching. It's been fabulous. I know that these are challenging times to preparing for AP exams is always stressful. We've got some kind of dark times, but Dr. Sowell and I are really committed to making sure we do a good job reviewing and giving you lots of practice. So hang in there. You guys are doing a great job. Have fun with biomes tomorrow, and I'll see you next Monday.
Hello, AP Environmental Science students. Glad to see you again. Welcome back. Let's dig into some APES. So my name is Dr. Sowell, and I teach APES down here in Jacksonville, Florida. So just as a quick reminder, remember this is when our exam is May 18th, and there are the times there on the left-hand side. And here are 2 questions, what percentage they're worth for the exam, and then 1 and 2 down here give you the description of the skills and practices you'll need for those 2 questions. So let's do our little warm-up, and this is the homework assignment from Ms. Fassler's last video lesson on biogeochemical cycles, in particular the carbon cycle. So there's an introduction paragraph up here, and then it says, scientists are interested in researching how increasing soil temperatures will affect the rate at which soil microbes decompose organic matter. They design a laboratory experiment in which they measure the change in the amount of CO2 in soils incubated at different temperatures for a period of 5 days. All soils were collected from the same location. So the first question you were asked is to explain how carbon enters the soil. So here you could have said something like the carbon enters the soil from organic matter from dead plants and animals, and then the carbon enters the soil when they die. How does that carbon get back into the atmosphere was B, and that's through the decomposers. Carbon in the soil is returned to the atmosphere as CO2, and the decomposers in the soil break down dead plants and animals. And then through their cellular respiration, CO2 pops back in the atmosphere. So C and D were about the experiment itself, and this is definitely going to be a part, or a version, or something like this is going to be part of FRQ number 1, experimental design. So identify the independent variable. The independent variable was the temperature. That was the thing that was changed by the scientist. What was the control? Remember, the control is the group that is not exposed to whatever variable you're exposing them to. In this case, it was the temperature. So the experimental control is the soil sample that is not incubated and left at room temperature. And then there's a describe question. How would the CO2 change if the temperature was increased to the point that killed the soil microbes? Well, there would be less CO2 generated for the atmosphere because the decomposition would come to a halt with no decomposers. So hopefully you got some of those right, and that was a good review of Ms. Fassler's talk on biogeochemical cycles. And again, this pattern will repeat. I'll leave you today with an FRQ or part of an FRQ to do. Ms. Fassler will go over that next time. All right, so here's where we're going today. We've got the biomes. Now, I'll go ahead and say up front, the biomes, there's a risk sometimes when you learn biomes, it's just a list. Here's a biome, 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 here's a biome. And it all kind of gets confusing in your head. So it's best if you can find ways to group them, compare them, or contrast them. So I'll try to do some of that today, but I am going to have to resort at some point, you'll see, to kind of a list format. But I'll try whatever I can to make it a little bit more connected and robust and big picture as opposed to just a laundry list of biomes. And then particularly we're going to focus on practice number 1, concept explanation. This is your ability to explain environmental concepts in context. All right, so we'll come back to this practice toward the end. So what do you need to know? So this is Unit 1, Topic 2, and Topic 3. So Topic 2 is the terrestrial, Topic 3 is the aquatic or the marine. Actually, all the aquatic, marine, freshwater. So by the end of this section, you should be able to describe the global distribution and principal environmental aspects of terrestrial biomes. So distribution, where are they? And there's a pattern to that. And then once you know kind of where they are geographically, what are some of their characteristics? What makes a savanna different from the tropical rainforest, for example? So to get there, we will describe the 9 major biomes of the terrestrial. And then for each of those 9, we're going to talk about climate, the organisms there, the distribution of resources, and look at some impacts, including climate change on each one of those biomes. So let's first of all define what a biome is. So a biome is an area of the planet that can be classified according to its climate and the organisms that have adapted to that particular location and climate. So just as a quick review, remember, we might look at this grassland here and notice an individual species of grass. So this one organism right here, this grass. And all the grass of that species are population. All the different populations, the populations of insects, of birds, of small mammals, whatever it might be, all those populations put together is a community. Add in all the abiotic factors of light and heat and lithosphere, that's the ecosystem. Well, biome, and this goes from kind of small to large, obviously. Biomes are even bigger than that. In fact, biomes contain multiple ecosystems. And they're just not clearly defined. It's not like North America is this biome or Georgia is this biome. There's some fuzzy areas, some fuzzy transition zones. And then when you start learning about, or not learning, reviewing your biomes, and you probably recognize this before, if you start to Google some of the biomes, some places call the same biome by a slightly different name. So you got to be careful of which classification system you're looking at. We use one that has 9 and they have certain names to them. So if we just start from a big picture, let's just look at the map of the world. Even if we don't label the biomes, you should start to see some patterns, even if we just look at colors. My eye is always drawn here to South America, to this tropical rainforest, and you can see this green is repeated several other places in this tropical equatorial region here. And then we could also go to the very top and look at this light blue, which is the tundra, and that has a similar pattern of latitude. So one of the guiding principles of biomes is noticing where, in terms of latitude, they're located. So here are our 9 biomes that we must learn. So first of all, we've got the taiga. Now, I put boreal forest next to there because those 2 words are interchangeable. Sometimes you'll see it described as taiga, sometimes you'll see it described as boreal forest. You should know both of those. Our particular curriculum uses the word taiga, but as you're studying and looking at other resources, boreal might pop up. So we have temperate rainforests, temperate seasonal forests, and tropical rainforests. These first 4 are grouped together because they're all forests, and we're going to walk through each 4 of these so you can see similarities and differences. And then we move into shrubland, which is not dominated by trees, more of shrubs. And you'll notice in parentheses it says chaparral. Chaparral is what the shrubland is called in California. And so sometimes this word chaparral is used as a replacement for shrublands. Then we're going to do our 2 grasslands, the temperate grassland and the savanna, and then we'll do our 2 deserts, the hot desert and tundra, which is pretty much a cold desert. So that's the pattern we're going to go through today. So just as a quick reminder, I'm sure this is a review for you, but remember when we're talking about the tropical region, we're talking about the area above and below the equator, and the areas above and below that are temperate, because the words temperate and tropical pop up in the names of those terrestrial biomes. So it's just a nice reminder of what those words mean. So again, here's our equator, area above and below that is tropical, and above and below that is temperate. All right, so throughout throughout today, I'll be showing you different climate graphs from different biomes. Now, sometimes you'll see these called climatograms or climatographs, but all they are a visual representation of the climate of a biome. So let's just kind of deconstruct the graph here for a minute. The first thing I want to point out is the x-axis is the months. This is a calendar year, so each of these bars is happening on a month. Then these bars represent precipitation. Precipitation is over here on the left-hand side y-axis, and then on the right-hand side we have temperature. So precipitation in the bars, temperature above. Now, if we just look at this biome, you may want to think, well, this is pretty warm. You know, this is a constant warm temperature. We don't see a big seasonal fluctuation, so it's hot pretty much most of the time, and a lot of rain. Well, it's a tropical rainforest. So that's what you should be able to do. Look at climate and precipitation and temperature and try to understand the connection to the specific biome. All right, a lot of the images and climatographs I'm going to grab today come from a really great resource for HHMI Biointeractive called Biome Viewer. It is free, it is really dynamic, and it's a great place to review all these biomes. So instead of going to the website, what I did is I just videotaped myself on the screen using Biome Viewer. So if it'll load up here, let's see if it's going to load. I'll come back to it. Yeah, we'll just come back to it. But it's a nice little video to talk about. Okay, so you'll notice here it first starts out with just the terrain. So this upper left-hand side says terrain, and you can grab onto the globe and actually spin it around and move it to different locations. You can also flatten it out so it looks like a flat map, but it's also kind of fun to spin the globe and you can zoom in and zoom out. But I first wanted to just put it onto terrain. Well, if you go over to that top left section, you can actually toggle it over to where it says precipitation, and you can go through and change the months and see how the precipitation, in this case over the continent of Africa, changes over the course of the year. That's just kind of interesting to look at. And you can switch it again at the top left to temperature and do the same thing. Look at how temperature changes over the course of the year in one particular location. And since biomes are really defined by their temperature and precipitation, that's what we look at as biomes. So all the biomes are listed on the left, and all you have to do is go to a place on the map, click it, and it'll put a little pin in it, and at the top right, it'll bring up a climatogram, and that'll tell you obviously the temperature and precipitation. But if you click on more, it'll blow that up so you can see it really in detail. On the left-hand side, you'll also be able to click onto a description of the biome. So in this case, a savanna. It gives you a description of where it's found, what it looks like. And on the right-hand side, you can click and look at some typical wildlife. In particular, it shows you the species richness for reptiles, amphibians, and mammals. And you can also toggle on and off levels of threatened or endangered or critically endangered. So it gives you more than just the climate and precipitation. It gives you wildlife as well. The last little feature I want to show you is the compare button. So you can pin one place and then click on the word compare and then click on another place. And what that'll do, it'll open up both of the views of the climatogram and you can compare them side by side. So for example, this is the temperate grassland in Russia on the left and the tropical rainforest on the right, and you can compare those two. So that's what Biome Viewer does. I highly recommend it. Great way to review. All right, let's keep trucking here. So first one I want to look at is the taiga. So again, located between 50 and 60 degrees. This is also known as the boreal forest. Low precipitation, low species diversity, low temperatures, some permafrost, not a lot. It's patchy. And interestingly enough, there's none in the southern hemisphere. This is all northern hemisphere. So if you'll notice on the Biome Viewer, it's called boreal forest, not taiga, but you can see it's this dark green in North America and over here in Asia and Europe, dark green. So let's look at two of the climatographs. So this is from Canada on the left and Russia on the right, very far away from each other, but their climatograms look pretty similar. We have seasonal fluctuation in temperature, pretty cold though, and pretty low precipitation. In terms of species richness, it's pretty low. Like I said, the biodiversity of organisms is pretty low. It's dominated by trees. Now, what kind of trees is unique? It's typically conifers, evergreen conifers, things like spruce, fir, and they've got those little needles instead of broad leaves, and those needles are very well adapted to drought conditions because there's not a lot of precipitation here. The organisms here, the actual animals, are medium to small size, some large ones, but no matter what, you've got to be adapted to the cold, so you're going to have insulating feathers or fur, or maybe even some long distance migrations to leave the boreal forest when it gets too cold. In terms of human impacts, there's really not a big threat from agriculture because the soil quality is pretty low. It's really cold, so short growing season, there's not a lot of decomposition going on in the soil, so you don't get that really rich egg horizon humus nutrient layer that we would get elsewhere. But what it does do is it grows big trees, very slowly though, and it's a great source of lumber pulpwood, huge source for industrial wood. So clearly the biggest anthropogenic threat is logging. There is some mining for natural gas and oil, and clearly climate change can affect this biome. As the planet warms and climate changes, it may shift where these biomes are located. So this is just a really beautiful picture. The reason I put it up here is a picture of a lynx, and this lynx is living in the boreal forest, again, also known as taiga. If we zoom in on its face, you can see a beautiful eye. So this is the eye of the taiga. Let's get going. Let's do temperate rainforest. So temperate rainforest is located here in the Pacific Northwest, also in Europe and some in Asia as well. You'll notice that in Biome Viewer it's called temperate coniferous forest. Coniferous just means conifer trees, evergreen trees. It's got warm summers and cool winters and some pretty adequate rainfall. So you can see that this on the left is from Japan and on the right is from Germany. Both temperate rainforests, both pretty similar in precipitation and temperature. And if we compare species richness, it's much more species rich and biodiverse than the boreal forest was. It's again dominated by evergreen trees, these conifers, but also lots of lichen and mosses and ferns, these epiphytic plants. And then typical animals would be deer, elk, plenty of reptiles and amphibians. So in terms of the threats to the temperate rainforest, again, not a lot of soil fertility in terms of decomposition of the leaf litter because of those needles. So agriculture isn't a huge threat. What is a threat? Again, is logging. So we've got some very large trees that grow here. And so this is especially important during our look at old growth forests. Remember, old growth forests are forests that have never been logged. And over here on the right hand side, you'll see a picture of the northern spotted owl. We're not going to go into that today, but I would highly suggest if you're interested in learning about a great situation that explores the Endangered Species Act and really the politics and the economics of environmental legislation, that's a great case study to read about the northern spotted owl and the old growth forest of the Pacific Northwest. Really interesting. All right, let's do temperate seasonal. This is our third forest. So we did boreal forest up here, the taiga. We did this coniferous forest, the tropical or the temperate rainforest below that. Now we're going to go into temperate seasonal. Seasonal is another word. Well, you know what seasonal means, but it also can be called temperate deciduous, meaning that the leaves are going to drop every year. So we can see a good chunk of this in the eastern part of the United States, over here in Asia, and also on the eastern coast of Australia. Now, this climatograph on the left is from Raccoon, Kentucky, and on the right is from somewhere in New South Wales and Australia. They are both temperate seasonal forests, but you'll notice while the precipitation is pretty the same, the temperature is quite opposite from each other, and clearly because it is in the southern hemisphere. In terms of species richness, it's got pretty strong species richness, much more than like a boreal forest or a tundra. Common animals are deer, bears, lots of small mammals and birds. But again, it's dominated by deciduous trees that drop their leaves every year. In terms of human impact, because of that dropping of all the leaves and because of the warmer temperatures, we get that really strong buildup of organic material in the soil. So that leaf litter in the over-horizon really decomposes down into that rich humus of the A-horizon. And so therefore agriculture is probably more of a threat here, as well as logging and just urbanization, growth of cities. All right, let's look at our last forest, the tropical rainforest. This is the one we're very familiar with in terms of the Amazon rainforest, but it's also located here in Africa and down here in Southeast Asia as well. And you probably could recognize this climatic at this point. So very high temperatures, very high rainfall, very characteristic of a tropical rainforest. Really biodiverse area, huge species richness, lots of NPP. So remember, the NPP is the net primary productivity, the battery that kind of feeds the rest of the food web. There's so much vegetation that the rate of photosynthesis is so strong that it has lots of NPP to support a very complex food web in the tropical rainforest. Heavy canopy, and so meaning like heavy tree layers at the top. And so because of that, the plants there have learned to compete for the sunlight. So sunlight is a living factor for some of those plants, especially the ones growing underneath the canopy. But 2/3 of the terrestrial species on the planet are in this biome. Wow, that's a cool statistic. In terms of threats, clearly there's high decomposition here, so you would think that the soil would be very fertile, but actually it's quite the opposite. There's tons of leaf litter, tons of decomposition, so you would think that it would build up and create really fertile soil. But in fact, there's so much living vegetation that as soon as things decompose, those nutrients are assimilated right back up into the plant. So it doesn't have that buildup of nutrients that you might find in a grassland, for example. So again, agriculture, logging, human population growth, the typical suspects here. All right, so those are our four forests. Now we're going to go into this weird middle place, the shrubland, also called the chaparral. chaparral. It's a pretty rare biome. It's typically in these coastal regions along California on the west coast of the United States, all around the Mediterranean, and there's some here in Australia. You'll notice that it's got hot, dry summers and cool, moist winters. That hot, dry summer is going to become important when we talk about the fires there. So you can notice here in its climatogram, temperature, and precipitation, but there's hot, dry summers there in the middle. So here's some pictures of some chaparral shrubland in California. So again, mild winters with high precipitation and dry, hot summers. So that results in pretty not so fertile soil because of heavy leaching by those winter rains. But because of this dry, hot summer, it's very prone to fires, natural fires. So that is a characteristic of shrubland that's pretty unique. Therefore, the shrubs, the vegetation there have adapted to this dry and fiery conditions. Typical organisms might be deer, lizards, jackrabbit, and then in terms of threats, human development and livestock raising. All right, so now we're going to go into our two grasslands, temperate grasslands and savanna. So we're going to kind of squish them together in our talk. So temperate grassland, known primarily as prairie, pampas, veld, or steppe. This biome is largely devoid of trees and has large seasonal variability in temperatures, but relatively low precipitation. So grassy, very grassy. And then we have the savanna with warm temperatures and seasonal rainfall. This biome consists of a mixture of grasses and sparse trees and is found within tropical or subtropical latitudes. So we have a grassland in the temperate region here, and then we have a grassland called the savanna in more tropical and subtropical regions here. So similar characteristics, but different locations. And we can see there are two climatograms here. So this is the temperate grassland, you can see there, and this is the African savanna, and you can see that. So we see much more of a seasonal rainfall event here in the savanna. All right, desert and tundra. Those are really deserts, one hot and one cold. So a desert, we all kind of know what a desert is. So extreme cold temperatures, very treeless landscape. And then tundra, it's the same thing, just cold. So desert, hot and dry, tundra, cold and dry. And so you can see desert here, tundra up north. So both deserts, just differences in temperature. Again, you can see the two climatograms. So the desert, high temperature, tundra, low temperature, but both very minimal precipitation. So I just want to pause really quick and talk one more thing about the tundra. Incredibly low productivity, low NPP, low species richness. And one of the things that connects to is ecosystem stability. We know that typically ecosystems with large species richness and wide biodiversity are more resistant and resilient in terms of their reaction to disturbances. So in a place like a tundra, that's just the opposite. So disturbances can have a much more long-lasting and dramatic effect because there's such slow growth and low biodiversity, it takes a long time to come back. So things like oil and natural gas exploration can be pretty impactful. And the next thing I want to show you is this picture down here. This is permafrost, that permanently frozen ground. And this permafrost locks in a lot of organic material. Unfortunately, because of climate change and global warming, we're seeing the melting of permafrost. What happens when that permafrost melts? Decomposition, which was before stopped because it's frozen. Now the decomposition starts again. That puts more greenhouse gases into the atmosphere, which in turn causes a stronger greenhouse effect, which melts more permafrost, which puts more greenhouse gas. So that's that positive feedback loop that we mentioned a few times. Positive feedback loop, good example of that. All right, so the way I want to end with the terrestrial biomes to show you this diagram, which I absolutely love because it's a different visual way to represent the different biomes. So you can see on the x-axis down here is temperature and the y-axis up here is precipitation. So down here in the corner desert, this is hot, very hot, and very dry, low precipitation. If we go to the highest amount of precipitation, tropical rainforest, this is hot and wet. And if we go all the way to tundra, this is cold and dry. So one of the things that I typically have my students do is cover up these words and see if you can place each biome in its correct category. It's a good review for all the terrestrial biomes. All right, so that's the land. Now let's go to the water. So by the end of the section, you should be able to describe the global distribution and principal aspects of aquatic biomes. So to get there, we're going to describe freshwater first. So we'll look at the freshwater, and there's two big categories there: free-flowing water and standing water. So the flowing water will be lakes and streams, or I'm sorry, streams and rivers, and then standing will be ponds and lakes. And then we'll go into the ocean, to the marine biomes, and that's going to be the ocean, the reefs, the marshlands, and the estuaries. So in terms of freshwater biomes, the first one is streams and rivers. And clearly this is a flowing water ecosystem. The water is moving, sometimes quite rapidly. And because of the varying types of rivers, you can have varying conditions and therefore varying organisms too, depending on whether it's upstream or downstream, how much canopy cover, how much shade the trees are giving on top of the stream or river that might change the temperature, how deep it is, how fast it's flowing, the volume of water, the discharge of water, the turbidity, the cloudiness. So even salinity. So I live here in Jacksonville, Florida, and we have the St. Johns River, which flows north and it kicks right into the Atlantic Ocean here in Jacksonville, and we can notice an increase in salinity as it gets closer and closer to the ocean. So not all streams and rivers look the same. And in fact, topography is one of the big factors that will do that. Now in this diagram, it's showing how the headwaters of these streams start in these high elevation with melting snow and ice. Now here in Florida, we don't have mountains nor do we have snow or ice. A lot of our streams and rivers are fed by springs that come out of the ground. But either way, the headwaters are charged, they start to flow down. You start to get this meander, this wiggly back and forth before it discharges into the ocean. One of the words here is floodplain. Just remember the word floodplain is the area on either side of a river that will flood, either on a regular basis or pretty occasional basis. But typically those floodplains are more fertile because the water floods up, deposits some of that nutrient-rich sediment, and then goes back. So we may have lots of agriculture in a floodplain. All right, so some human impacts. We talked heavily about this when we were talking about Unit 8 on aqua pollution. I talked a lot about nuclear runoff, wastewater release, and agricultural runoff impacting water. So here we have pollution. Pollution is clearly a big impact on freshwater biomes. We have nutrient pollution like eutrophication. We have acid mine drainage, and we'll talk about that when we get to mining coal. You can also have sediment pollution from construction or erosion, just making the water more turbid and reducing photosynthesis. We could divert that water for human use, and we could build dams. So dams would clearly build up sediment upstream instead of letting the sediment flow downstream. It might build up here, and then clearly it's habitat fragmentation. These two habitats have now been fragmented. And like I said before, not all streams and rivers are the same. So on the left here is a pretty shallow, fast-flowing river, and this is again the river I live near, St. John's River, which is really slow moving and pretty big. Florida's flat, so we don't have a lot of elevation, so this river flows very slowly. It's pretty turbid from all the tannic acid of the decomposing leaves, so it looks very different. And differences in rivers and stream physical characteristics inform the kind of organisms that live there. We're going to take a look at a few minutes about Dr. Mary Power, and she is studying the relationship between the flow of a river and the organisms that live there.
I've always had a deep wonder and fascination about the natural world, and I'm especially intrigued with how species interact with each other and also with their environments. My scientific research focuses on rivers and the food webs they contain. Rivers are extremely dynamic habitats. They can change dramatically from season to season and from year to year with the amount of water that's flowing through them. Yet rivers are also habitats with clear boundaries. With a little work, you can follow the key river food web members as they go through their daily lives and watch their numbers and their interactions change over time. One question that drives my work is, how does the amount of water flowing through a river affect its food web and the state of river ecosystems as a whole? To answer this question, I've been studying the Eel River in Northern California year after year for the past 25 years.
So I just want to pause it here to focus your attention. Dr. Power is now going to talk about her experimental design, how she's setting up her experiment, her methods, how she's doing data collection, to not only focus on the flowing water ecosystem, but also her experimental design and her research.
That drains much less area. Our Eyes on the Eel survey is 10 Berkeley students and me, and we go out 3 times a summer. We focus on 3 groups of organisms to get a picture of the river's food web: the fish, the aquatic invertebrates, and the algae. Now, algae are the base of the food web. They are at the lowest trophic level. The amount of algae and the type of algae both determine the health and diversity of the insects that eat it, and in turn, they determine the food supply for the fish that eat them. And then there are bigger fish that feed on little fish, so all of this energy is flowing up the food web. We always start with the big fish. That's because the big fish in the pools spook most easily, so we need to count them first or we'll scare them off when we're taking our other measurements.
When we start with the tributaries, one thing that is true for most tributaries is the they're cold. So if I want to be dry suit, I zip it up. I have a dash tail on my arm. I typically know the type of organisms I'm going to run into in the tributaries, and I have different size classes which relate to different ages that we're interested in. You need to move very quietly, very slowly, and you don't want to be spooking fish. It was such a neat experience to get to put your head underwater and enjoying this aquatic world that you never get to be part of otherwise.
Once the larger fish in the pools have been counted, we count the juvenile fish from the shore. We take counts in 3-minute increments, carefully noting the species and size class of the fish.
2, 1, stop.
When we finish counting the fish, the team moves on to measuring the second component in the food web, the amount of algae that's there, or what we call the algal standing crop. The quickest way to get a picture of what the river habitat looks like at the moment is to throw a measuring tape across the stream, so it's a cross-section. A river is essentially a collection of pools connected by shallow riffles. We measure our cross-sections in both pools and riffles. And then you make a measurement from the water surface down on the stream bed at even intervals. The depth is 19. You can quantify the texture of the substrate. Is it cobbly, bouldery, is it sand, is it mud? What are the major algae that are growing there? That's enough information to draw a picture of what the algal standing crop is doing and how it's changing seasonally. When we're done surveying the habitat and the algae, we move on to the aquatic invertebrates. The riffles where a lot of the bugs grow. We take an aquarium net and you sneak up on a rock and you pick up this rock skillfully and quickly, and then you invert it over a white plastic tray. You're looking at these tiny things, but they are so diverse, and some of them are so brave. There's little predators walking around trying to pinch the ruler that you're trying to measure them with, and we just get so fascinated. We tried, let's take a sample of this home because it might be something unusual. When we are keeping track of the species, we can follow their densities from year to year. When I started studying the eel 25 years ago, I had no idea of what controlled the river food web. What we have discovered is that water flow in the river over the entire year determines the state of the summer food web.
So our experiment really lends itself to understanding the relationship between the water flow and the organisms that live there. Really, really cool. Sounds like a great job. I'd love to be doing that. So let's now look at lakes and ponds. So these are standing water ecosystems. Now, an interesting aspect of the lakes and ponds is light and how low down light will penetrate. So over here on the shallower sides of the lake or the pond, we have the littoral zone. And this is where we have rooted vegetation. We have lots of productivity and biodiversity over on these shallower areas where light penetrates all to the ground. And in the limnetic zone, the open part of the lake or pond, and in some lakes or ponds, not all, it may be deep enough that we have a profundal zone where light does not penetrate. And so therefore, the type of productivity and microorganisms and biodiversity up here in the light is going to be very different from without light down here. We may have slower rates of decomposition, maybe some hypoxic areas, but a very different community than we would find in the littoral zone. And whether or not you're getting it from standing water or free-flowing water, lakes, ponds, river streams, that's where we get our drinking water. I know here in Florida, we draw ours from the Florida aquifer, so we're drawing it from our groundwater. Some places draw drinking water from surface water, but whether it's surface or ground, it's all connected, and that's important thing for us to remember. All right, let's get salty. So let's go to the ocean and the marine environment. So this is a nice poster to start with. It's from National Geographic, and it was made of the Gulf of Mexico right after the BP Deepwater Horizon oil spill. So you can see down here at the bottom right is the broken pipe from Deepwater Horizon and this plume of crude petroleum, all these hydrocarbons getting into the water. So that's not the story we're talking about telling here today, but I just want to point it out. So what you can also see is the really varied communities here. So up in this tidal area where the water is pretty shallow, the communities are very different than what you find in the open part of the ocean, or even down into this benthic or bottom dwelling area. But again, it could get deep enough, or it does get deep enough in the ocean where light does not penetrate. So depth of light, nutrients, salinity, all of those things are really going to create a variety of different communities in the ocean. Again, open ocean communities are a little different than tidal communities just because of these varying abiotic factors. And again, light is a big part of that. So just as a vocabulary reminder, benthic means bottom. So anything living on this bottom, whether it's shallow or deep, is called benthic. Pelagic is the open part of the ocean. And then we have this dark aphotic zone where we do not have light. So therefore photosynthesis is not going to happen. We may have something like chemosynthesis that we would see in the hydrothermal vents, DT vents. Coral reefs are another marine biome. I talked a lot about this during Unit 9 under human impacts when I talked about coral bleaching. But overall, this is a picture of a coral reef. It's a benthic habitat, and it typically has to be in shallow waters where light can penetrate. Why? Because the coral polyps, the little tiny individual coral polyps, inside their tissues, they have a photosynthetic symbiont. They have an algae living in their tissues. That's what gives the coral reefs such beautiful colors. It's because of all the algae living in their tissues. And so if they get the majority of their food from algae, they better be up somewhere where light can get them. So that's why you typically find corals in shallow habitats. And then they secrete this calcium carbonate that forms the whole reef structure, and then that just kind of builds up over time. But huge biodiversity, incredible species richness. But the biggest threats are coral bleaching and ocean acidification. Two things clearly linked to climate change. Coral bleaching comes from when sea surface temperatures become too hot. The corals spit out their symbiotic algae, and if that goes on for too long, they starve to death because the algae was what was giving a lot of their nutrients. When they kick those out, they risk dying. And then the other thing is ocean acidification, which really affects the rate at which these organisms can build their shells out of calcium carbonate. So not only does ocean acidification affect coral reefs, but any organism that has a shell. So now let's go to a marshland. So a marshland is a coastal wetland. So remember, a wetland is an area where the soil is saturated with water at least part, if not all of the year. Marshes typically have brackish water, and the organisms that live here have to be adapted to rising and falling tides. One of the characteristics of a marshland is it's dominated by grasses. As opposed to a swamp, which is dominated by trees, a marshland is dominated by grasses. And they serve some really important roles for us. Talked about this when we talked about water back in units 8 and 9. But the benefits are mainly it helps to clean the water. So as the water flows down from inland out to the ocean, it almost acts like a speed bump. So it slows the water down and lets some of the sediment and pollutants filter out. And then all of these grasses are huge absorbers of nutrients. So any nutrient pollution that might be in the water setting to the ocean, some of it is assimilated into the marsh grasses before it gets to the ocean. So it has some really clear human benefits. Then we got estuaries. Estuaries are the nursery grounds of the ocean. So it's with flowing freshwater stream or river meets the ocean. Water is usually brackish. Brackish means not salt, not fresh, somewhere in between. Again, because there's tides up and down, it's going to affect the depth of the water and the salinity of the water. So organisms there have to have adapted to those changes. It's an insanely fertile ecosystem. Huge NPP, huge species richness. And again, it's a nursery. It's characterized as a place where lots of larval stages of fish and shellfish and other organisms spend their time because it's a safe habitat for them to grow up in. Now, I'm not going to have you do this FRQ right now or for homework, but I just want you to make a note of it. 2003 FRQ question number 3 is a great review of estuaries and typical wetlands and some human impacts on those wetlands. So I highly recommend looking at 2003 question 3 and then looking at the scoring guidelines with the answer keys. All right, the last little part of the ocean we need to talk about is all this algae, this ton of phytoplankton that is in the ocean, and it serves as the basis for the marine food web. As these phytoplankton drift and flow with the currents and the waves, they're eaten by zooplankton, which are eaten by smaller fish and bigger fish and bigger fish. So this is almost like the battery of the ocean. It's what's taking that energy from the sun and filtering it right down into the food web of the ocean. Does another huge benefit for us, gives a lot of our oxygen. A huge chunk of the oxygen in our atmosphere comes from this phytoplankton in the ocean. And if it's making oxygen, it's sucking down carbon dioxide. And anything that does that in light of climate change is good. This is just a nice little graph or image of the world. It shows the really high levels of chlorophyll in the oceans, so you can see the vast amount of productive algae that's out there. All right, so that was a fly through of terrestrial and aquatic ecosystems or biomes. So let's just do a quick question check. So I'll give you 30 seconds for this question. So the answer here would be D, an increase in temperature and precipitation. This one says, which of the following best describes soil in many tropical rainforests? Is it lack horizons? Are they quickly depleted if the forest is removed? They are similar to soils in grasslands. They're well suited for growing a wide variety of crops. They are deep and well drained. And actually it is B. And we talked about that lack of build up nutrients within the horizon of a tropical rainforest because the plants assimilate up so quickly. This one says the major biological source of dissolved oxygen in the ocean comes from, we just mentioned that, phytoplankton. All right, so this is a question I made up. See if you can determine which one of these biomes is best represented by this climatogram. I'll give you 30 seconds. All right, and the correct answer is tundra. Tundra, very low precipitation and cold temperatures. So where did we go today? We did the terrestrial biomes, the aquatic biomes, and particularly with the terrestrial biomes, hopefully you started to see some patterns between them and among them, and the main things that distinguish one from the other in terms of latitude, in terms of temperature, in terms of precipitation, and in terms of the organisms that are adapted to live there. So for this practice number 1, concept explanation, remember this is what the description of it says. It is important to make clear the distinction between memorizing details and demonstrating an integrated understanding of how a concept or process connects the overall function of the environment. Basically that's saying, don't just memorize what a tundra is, be able to explain some of the environmental processes that are happening within the tundra. So here's an example. Explain the relationship between deciduous trees in a temperate seasonal forest and soil fertility. So take a few seconds and think what you might right there. So before we look at the answer, let's just look at the skill a little bit more. So explain concepts and processes. So the first part, the easiest part, is explaining characteristics, explaining concepts. Then it gets into explaining the relationship between components, explaining how a process occurs, explain the relationship between structures and functions. So these are some characteristics or some typical things you might be asked to do on one of the FRQs on the exam. So in terms of the answer here, I wrote, deciduous trees in a temperate seasonal forest drop their leaves annually. Decomposers break down this leaf litter and add nutrients into the soil, thus increasing soil fertility. That's what I would have written. All right, so here's your homework. So your homework again is going to be an FRQ or part of an FRQ. And remember, I know I've said it a bajillion times, but I'll say it one more time. These task verbs matter. Know the difference between identify, describe, explain, yada, yada, yada. So here's the question I would like you to do. This is called worm invasion. So I'm going to read this first part to you. And then for homework tonight, you're going to do A, B, and D. So it says, a researcher studying the ecology of deciduous forests outside of Fremont has made an alarming discovery. So automatically you see the word deciduous, so you know this is probably a temperate seasonal forest. While taking an inventory of the species present on the forest floor, Professor Tate discovered many earthworms of an Asian species not previously known to live in this area. The Asian worms, unlike native worms, have voracious appetites. The forest floor is home to a myriad of species that live in the leaf litter, which is composed of several years' accumulation of slowly decomposing leaves. Dr. Tate explained that the leaf litter is critical to the survival of local species of forest lands. He has found the Asian worms, unlike the indigenous cousins, consume the entire layer of leaf litter in a single season. He said, quote, this sets the stage for the takeover by invasive exotics such as Japanese stiltgrass. Dr. Tate and other scientists are exploring strategies to control this Asian worm. So what I'd like for you to do for homework tonight is to complete A, B, and D, and Ms. Fassler will go over the answers with you next time. And hopefully you can draw a little bit of what we talked about in the biome today. Again, if you have connectivity issues or know anyone who does, please reach out to this URL because connectivity and internet access at this point is not only critical for what we're doing today, but it's going to be critical for you actually taking the exam in May. So thank you again. Hope you have a wonderful weekend. Bye, apes.
Hi, students. Thank you for joining me again in our virtual classroom. We're going to dig into Unit 2 today. Let's take a minute and you want to get out your homework that you did on Friday with Dr. Sowell. I'm Ms. Fassler and I teach at Marshfield High School in Marshfield, Wisconsin. Last week on Friday with Dr. Sowell, if you were doing the live video classes, you took a look at biomes and you learned about how biomes are, the pattern of biome distribution is largely determined by climate, which is largely determined by latitude. And I just wanted to share with you that while Dr. Sowell is down here in Florida sweating it out, I'm at about 45 degrees north latitude up here in northern Wisconsin. We had about 8 or 10 inches of snow yesterday. So I know there was some severe weather around the country. I hope everybody is doing well. And thanks for hanging in with us as we start to get really deep into the review for our exam on Monday, May 18th. What we're going to focus on today is really this skill set that is common to both of the 2 free response that you're going to answer. Although as we go through a couple practice questions, we'll look at designing an investigation. I know that's one that makes students a little bit nervous. Maybe we'll have some more homework practice on that tonight, and we'll look at some solutions as well. So go ahead and grab that homework that you did on Friday where you looked at a worm invasion. So there's a free response question that you answered where you had to support Dr. Tate's assertion that the leaf litter is critical to the survival of local forest plants and include in your discussion the role of leaf litter in a deciduous forest ecosystem. So one of the best pieces of advice that your teachers were probably giving you, and Dr. Sowell and I as your virtual teachers can give you, is that when you read that prompt of the FRQ, don't just start puking out the first thing that comes into your mind. Take a minute because the writing will go rather easily. Take a minute and process what that question is asking you to do. And the first thing I would do if I were reading this is I would in my head kind of go through, what do we mean by leaf litter? Oh, that's all those leaves that are sitting on the deciduous forest floor. They lose their leaves. And how does having those leaves on the forest floor help in the plants of the deciduous forest ecosystem? So you could talk about a number of different things here, and I'll kind of go through these bullets of which were the most common kind of answer students would give. Leaf litter is critical to the survival of forest plants because, and I'm guessing a lot of you went with this first bullet point, maybe because we had just recently reviewed biogeochemical cycles and food webs and food chains. So you got that idea that leaf litter stores nutrients and that it's going to be recycled or decomposed and release those nutrients and make them available for the growth of plants. You could have also talked about the benefit of that leaf litter preventing soil erosion and loss of plant nutrients, providing shelter for seedlings to grow, absorbing and retaining water, which is important for plant growth, or kind of similar to that, assisting in the infiltration and percolation and thereby preventing runoff of needed water. The next part of the question should have been pretty easy. 3 seems like kind of a lot, but we had to describe 3 abiotic changes that would likely result if the exotic worms consumed all that leaf litter in the first year. They were that invasive species that just went to town and consumed all of that leaf litter. So there's a ton of different things you could say. You want to make sure that you don't just necessarily say something changes, but indicate how it might change. You can make an argument for either increase or decrease in soil fertility, changes in the nutrient level of the soil, changes in soil temperature, to be pH of the soil, increased rates of evaporation because I'm not holding that soil moisture in, reduced shelter area for animals that might live there. So all kinds of different things that you could have said would have abiotic conditions that would have changed. And then we get into a little bit of the experimental design. This invasive worm question is a little bit older, and although it's some good practice on experimental design, I don't think it's maybe quite as tight, or it's not guiding you real directly into that experimental design. And I think some of the practice that we give you, we're going to try to be a little bit more targeted. But let's see what you came up with here. The article talked about this native siltgrass. So a hypothesis could be that increasing the density of worms would increase the biomass of siltgrass. My independent variable would have been the density of worms. That's the variable that I control. My dependent variable in this example would have been the biomass, or how much silt grass grew as a result of that. Remember that your experimental control is always your sample group that is not subjected to that independent variable. So my control would have been a plot with no worms. And then if you look at other aspects of the experimental design that you could have talked about in designing your controlled experiment, we went through this in one of the earlier sessions about the idea of a large number of treatments. So how many test plots did I have? I want to replicate that. I maybe want more than one plot where each variable is being tested, and I can then average those results. How many times am I sampling each plot? How long am I going to let the experiment run? Maybe something about how I would actually measure the biomass of silt grass. So all other good components you could have included in your experimental design. Awesome. So now that we've got kind of that introduction to biomes, we're going to move into unit number 2 on the living world, understanding biodiversity. And we've divided unit 2 into 2 review sessions. I'll cover the first half of those learning targets today, looking at what biodiversity is and why it's important and how we measure it. And then tomorrow, Dr. Sowell is going to go into disruptions to biodiversity. And you'll notice that there will be a number of points throughout our lesson today that I'll kind of reference. Oh, if this disruption would occur, what would happen? Those are the things that you'll address tomorrow. So where are we going today? Well, we're still in this big idea that we were in unit 1 on interactions between Earth systems, that the Earth is this one big interconnected system. And we're going to look at that in terms of different levels of biodiversity. And in terms of skills, like I said, we're all really going to focus on this concept explanation. We'll do, as always, a little bit of environmental solutions, and your homework will give you a chance to practice again with experimental design. So let's get started. Where are we going today? What is ecological tolerance? This should look sort of familiar to you. It's one of our, it's one of the first learning targets in this section, but I threw it up at the beginning because we're really going to use this to help us understand some of those learning targets that follow. We came back and looked at this big idea in Unit 8 when we reviewed it. So if you watched any of them, or when we taught the information from Unit 8, so if you watched any of those videos, this should look pretty familiar to you. This is a really important diagram for me to be able to use to explain why changing the abiotic component of an ecosystem is going to impact biodiversity. That's where we're there. That's how we're going to apply this idea to explaining a bigger environmental concept. So remember that each species has a set of environmental conditions in which they can survive and reproduce, sort of those conditions that they're best adapted to through natural selection. And remember that this x-axis here can really be any abiotic factor. When I look at my essential knowledge statements, they talk about things like salinity, or maybe in our worm invasive species question, it would have been the amount of nitrate or phosphate that was in the soil available for plants. So any abiotic condition can be, I can talk about changing an abiotic condition and how the living organisms are going to respond to that change. And remember, when we look at this diagram, this is what I really want to focus in on here. And the misconception that a lot of students have that the minute I get a little bit outside that optimal range, that everything dies. And we'll model together and walk through a question at the end where we put this into practice. But remember, although I have this optimal and preferred niche, the temperature, pH, salinity, dissolved oxygen, where that species has evolved to really be successful, a slight change in any of those abiotic conditions doesn't necessarily kill off the entire population. I can have this zone of intolerance, but what we often see students do is indicate that things die, when in fact, small changes in those abiotic conditions are just going to mean that that organism is unable to thrive and reproduce at their maximum potential. So that's a misconception that a lot of students have, and they would say in a response that things die the minute they get outside that optimal range. So kind of good verbiage for you to have as you describe the ecological idea of ecological intolerance, and we'll come back and apply this in a bit. So let's go back to the first learning target of the unit and look at a review of what biodiversity is in general. Remember, when you first studied in Unit 2, we talked about biodiversity being represented by these different levels. I can have ecosystem diversity. That's really what you looked at with biomes in the last virtual session, right? That we can have polar, temperate, and tropical ecosystems. And the greater the number of different ecosystems I have, the greater the different variety of habitats and resources that I have. I can have species diversity. I can have lots of different species, and the greater my richness, my species richness, or number of species I have, the more I can hone in on those specialized niches. And finally, I have genetic diversity. Within my population of little chipmunks, I want a large number of individuals within that species, because the more individuals I have, the greater the different allele combinations, the greater genetic diversity I have, and the greater the likelihood that I'm going to have randomly by mutation an advantageous trait that may prove beneficial if there is some ecosystem disruption. So let's take a step back and dial in on each of these in a little bit more detail. We're going to go to genetic diversity first. So why is genetic diversity important? Well, remember, genetic diversity is the raw material of natural selection. It's all of those changes in allele combinations that are going to give the right trait for the right environmental condition that may happen in the future. It's also important because the death of individuals in a population can happen really quickly. But remember that genetic diversity is the sum of, it could be millions of years of adaptation of that individual, of the individuals within that population. So here's a good example. We've kind of been talking about elephants in terms of an endangered species. Notice I'm wearing my elephant garb today. So when we track African elephant populations, we can see that they have gone from 200,000 individuals down to, over a couple of decades, down to below 500,000 individuals. Each of those individuals represents a unique gene combination that once those individuals are gone, I will never have that specific unique gene combination back again. And we don't know what kind of environmental conditions might prove beneficial 10 years, 100 years. How can we predict 10,000 years, 100,000 years from now, what trait might prove beneficial to an individual, to a population? So we want lots of individuals, lots of genetic variation within that population. So that's getting at the value of genetic diversity. And you may remember when you studied this that you related that idea to what we call a population bottleneck. So the idea here is that as I have a decrease in population size due to some type of disruption that you'll look at tomorrow, I have a decrease in genetic diversity. I think we're okay with that idea right now. In other words, I have a decrease in the size of the gene pool, or a decrease in the number of different alleles within a population. Well, ecologists have called this a population bottleneck because we want to visualize all that original gene pool, all this unique gene combinations of every individual chipmunk in that population. And when for either an anthropogenic or natural reason, that population shrinks and we turn that bottle upside down and we shake out just a few individuals that were lucky enough to survive. Only a quarter of that original elephant population survived. And so they took with them only a quarter of the original gene pool, the original genetic diversity within its population. And so if I start off, each of these little different colored marbles represents a different allele within that population in the gene pool. If I start off with all this genetic diversity and by chance a small number of those individuals survive, even though my population by numbers may recover, we could see that elephant population was starting to creep back up a little bit. But remember, they have lost the genetic variation, a quarter of their population, a quarter of their genetic diversity. So now that we kind of understand this idea, we review it, we get the importance of genetic diversity and what can happen when I lose genetic diversity. It can result in a population bottleneck. Well, let's see if we can apply this or frame this in a real situation of a real population of organisms. So the whooping crane are kind of a cool story. They're a beautiful, large, majestic migrating bird. Their wingspan is over 5 feet tall, and they had a very healthy population prior to a lot of ecosystem disruptions. Their population went from over 10,000 to just about 15 whoopers left in the wild by 1940. One of the main causes for the decline in many migratory birds, obviously habitat disruption, but the use of lead shot for hunting, that lead ends up in the aquatic ecosystems where many migratory birds feed and they ingest that heavy metal neurotoxin. So you can see that the population is rebounding. They are coming back due to really concerted efforts on wildlife management, on wetland management, as well as captive breeding programs. This is just a cute picture showing people working at the International Crane Foundation raising chicks in captivity with the goal of releasing them into the wild. And what the workers do is they put themselves they clothe themselves from head to foot in this kind of white background, so hopefully they sort of blend in. And they use a little mama whooping crane puppet so that when they interact with the chicks, so that the chicks aren't imprinting on the human population, because the goal is to release them back in the wild. Well, one of the reasons we care about that population bottleneck, one of the direct consequences of that bottleneck is oftentimes that population will suffer anatomical abnormalities because of an inbreeding depression. And in the case of whoopers, they actually have, you may have heard of scoliosis. It's a curvature of the spine, something that many people in the human population would deal with. And it simply means that when I lose that genetic diversity and I have only a small number of individuals, this is all of the whoopers in captivity. So my choices for what individuals I'm breeding and mating is limited, and I often have to breed or mate closely related individuals, and I tend to have a reduction in the robustness of the population because of the likelihood that those harmful traits are going to become more predominant, that idea of an inbreeding depression. So let's move from genetic diversity to species diversity. Why is it important to have many different kinds of species within my ecosystem? And here I show you just a smattering of a variety of insect species within a certain ecosystem. So the term species richness simply refers to the number of different species, and I want a lot of different species because each of these insects, for example, is going to have a very different role. Some of them might bury dung, some of them might pollinate, some of them might control populations of other pests or serve as food for wildlife. So the more different species I have, the greater my species richness, the more I can hone in on those specialized niches and make sure that I'm using resources efficiently. One of the things that we want to understand about ecosystem diversity, if we go back up to that biggest level, we have genetic diversity, species diversity, and ecosystem diversity, is the greater the diversity I have, the more resilient my ecosystem is, the greater its ability to bounce back from some type of disruption that you'll look at tomorrow with Dr. Sowell. So the idea of ecosystem services supports the maintaining of ecosystem diversity. Remember, these ecosystem services are these life support systems that ecosystems provide for us for free. They have huge economic value. You probably remember throughout the year answering response prompts that ask you about an economic value of maintaining forests or coral reefs or whatever ecosystem it is that we're talking about. And remember that if we degrade these ecosystems, we're going to have to foot the bill for those services that they provide for free. There are 4 categories of ecosystem services. Some of these get kind of hard to remember, and our hope is that we can conceptualize the idea of an ecosystem service in general and try to give specific examples and understand what these different categories are. So I put them all in a chart here, so it's a little easier if you need to go back and review them. Let's just quickly run through these and see if we can give an example of an ecosystem that fulfills each of these ecosystem services, things we get for free. Well, there's provisioning. They provide for us. They give us food. They give us clean drinking water, medicines, lumber products, all of these valuable products that we get directly from ecosystems. So we have a lot of wetland ecosystems in Wisconsin, and one of our major exported agricultural crops is cranberries. And cranberries grow in those wetland ecosystems, and they need a lot of clean water. So we have a incentive to maintain wetland ecosystems for all of the economic benefit we get from the food that we harvest from them. We have regulating ecosystem services. These are processes that moderate natural phenomena, like how forests store vast amounts of carbon. The soil stores vast amounts of carbon. So we have an economic incentive to maintain these because they provide these services for free. Pollination of insects. So an example of that would be coral reefs, and the fact that they buffer storm damage, they absorb some of incoming waves, and if they aren't there, we have to spend a lot of money building some kind of artificial infrastructure that's going to accomplish the same role. Often underrated, but very at the heart of those of us in the apes community, are these cultural ecosystem services. Oftentimes we don't ascribe as high an economic value to these. I would argue they can be assigned an economic value. This idea of biophilia, or the well-being that I get when I am able to go out and birdwatch and hike through the woods and hear wild animals and interact with nature, get back to our roots. The idea that many indigenous people have a cultural tie to the land, many Native American populations. So the Arctic National Wildlife Refuge that has economic value for fossil fuels, but we don't put a price tag on the economic value to the indigenous populations that depend on the caribou that might migrate through that area. And then supporting ecosystem services. Again, they support us by performing underlying processes, much like tropical rainforests do, by providing us with oxygen to breathe through the process of photosynthesis. We'll get a chance to practice this in one of our questions in a minute. So let's do a quick timeout and check for understanding of the information we've covered so far. I think I just have 1 or 2 quick questions. Which of the following best explains how ecosystem stressors such as wildfires can affect biodiversity in an ecosystem? Take a minute and look at that one. How'd you do? Let's see. Now, Dr. Sowell and I both understand that you're not going to have any multiple choice on your national exam. It's just a 2 FRQ, but understand that we're still practicing some content, doing a quick content check with these multiple choice. And in addition to that, look how they're phrasing it. It's still the importance of being able to read carefully for understanding, because oftentimes in the question, you really have to tease out what environmental factor are they changing and how are they asking me to respond to that. So obviously ecosystems with more species diversity are more likely to recover from a disturbance. There's going to be a species that can fill that niche if that ecosystem has been disturbed. Which of the following can be used to assess the biological diversity of an area? This is the kind of thing they might even ask me in an FRQ. Boy, that'd be a great experimental design question. Maybe to assess the biodiversity of 2 different ecosystems. So I might want to measure the number of each species, the species richness, but note that I also might want to do some assessment of the genetic diversity, especially if my population is small. And we often do that simply by running electrophoresis. We run an electrophoresis gel, look at the DNA. They do that a lot with animals in captivity to make sure that when they're doing that captive breeding, they're crossing individuals that have the greatest genetic diversity. All right, let's move on to our next topic, which is a really exciting one on island biogeography. So you probably remember talking about this in terms of island size and distance from mainland, the distance from the mainland. Let's take a step back for a minute and look at the origins of this theory of island biogeography. Really, the concept underlies a lot of our understanding of ecological processes today. So I'm going to take you back and show you a short clip during some of the early work of famed ecologist E.O. Wilson. And what we have to remember in our study of environmental science is that ecology is a relatively new science, and things, ecological concepts and principles and processes that you take for granted were oftentimes discovered not all that long ago. So join me as we go back in time to when E.O. Wilson was a young graduate student.
It was during that period of exploration, I was also thinking about why different islands have different species and different numbers of species.
Wilson tallied the number of ant species on each island, and when he plotted them against the area of the island, he noticed an interesting relationship. An island that was 10 times bigger had twice as many species.
On islands elsewhere, reptiles and amphibians showed a similar relationship.
There actually was a rule, mathematical regularities, that nobody up until the 1960s had tried to reason out why it was like that.
Wilson discovered what he called a rule of thumb, a general relationship between the number of species on an island and its area. If this rule was indeed general, Wilson figured that if all the species were removed from an island, then the same number of species might repopulate it. But how could he test that? He suddenly remembered an extraordinary event.
On August the 27th, 1883, one of the greatest volcanic eruptions ever recorded laid waste to the Indonesian island of Krakatoa. Life on the island had been completely wiped out. That tragic event made Krakatoa the perfect laboratory in which to find out how species colonized and recreated an ecosystem.
What a great story, and what a cool control group that Wilson had. Actually, I believe Krakatoa just had an eruption yesterday or the day before. Go back and check on that. So let's break this model down a little bit and what the heck Wilson was talking about. He said that the number of species on the island reflects this balance between the rate at which new species colonize or immigrate to the island and the rate at which populations of established species become extinct. There's this equilibrium where those two rates intersect to determine the number of species on the island. Well, what I really want you to pull out of that video, that idea, that point that Wilson made, that this idea is sort of a rule of thumb for understanding other kinds of ecosystems. It's a really good model when we can expand that and use it to explain other situations, when this is a global concept that carries over from one scenario to another. So here's a picture of Central Park in New York City. This is an island of suitable habitat surrounded by a sea of urbanization where most, let's say, birds of prey, there's a lot of hawks that nest in and around Central Park. So they have this nice, safe island of habitat surrounded by a sea of unsuitable habitat. And in landscapes across the world, we see this idea, this global idea, that through disruptions to ecosystems, we have fragmented habitat into these little habitat islands surrounded by a sea of inappropriate habitat where the species that preside there can't live. So let's see if we can apply this to the bigger idea of understanding biodiversity and what happens when we have loss of species because of a disruption. I want you to see if you can describe how the size of the habitat will influence the number of species and then explain why. So let's kind of walk through this together. Here I can see I'm looking at island size, and remember this is a habitat island. I don't want to just picture this as a literal island out in the ocean. Well, the first thing I want to do is look at my axes. Independent variable is the area of the island, and the number of species depends on the area, and that is a direct relationship. The arrow goes up in a positive way. So I could say that increasing the size increases the number of species. Explain the relationship because there is an increase in resources where there's greater variety of resources or a variety of habitat and niches, therefore less competition for those resources, and I can support a larger number of different species. Let's take a look at the other variable that you might have remembered talking about during your APES class this year, and that is if I change the distance from the mainland. And again, picture this mainland now as Central Park, and this is all those maybe little parks that are located miles and miles away from that an animal would have to migrate to or immigrate to. So to describe that relationship, I can say that as I increase the distance, I decrease the number of species. There is an inverse or indirect relationship, maybe because it's unsafe or very difficult for that species to move. They might have to travel through all that developed area and come encountered with predators, or they don't have shelter, or maybe that's just too big an area for that species to move. Therefore, less species will be able to immigrate or move to that other habitat island. So now let's apply this model. Hopefully you have a pretty good feel for what island biogeography is, the way we can dissect that model and make sense of it. Now, what do we do with that understanding? If you watch Dr. Sowell's really cool lecture about endangered species and preserving them in Unit 9 on global change, you were introduced to this Y2Y corridor. That stands for Yellowstone to Yukon. So we have Yellowstone National Park down here up into the Yukon, a vast, I think it's a couple thousand miles. So these big habitat corridors, understanding island biogeography and what happens when we fragment intact habitat and how that leads to a loss of species. Well, now what do we do if we want to try to bring those species back or increase the population size of those different species? This is particularly important for large wildlife that need a lot of room to move. And so what we want to do is connect these fragmented island habitat islands so that they can have this entire space to move. When you look at our learning specific essential knowledge statement here, we're going to come back in a day or two and really dig into the generalist specialist. So we'll revisit this essential knowledge statement. It'll make a little bit more sense to us then. All right, let's do a little check for understanding here, and then we're going to go through a guided FRQ and look at some homework. So I think I only have 1 or 2 questions on the idea of island biogeography. For which of the following reasons do small isolated islands have a greater rate of extinction than large, less isolated islands? So we have the 2 different variables going on here. You got to tease out a little bit when you look at your options or choices. Go ahead and take a look at that one. And hopefully you selected letter D. Small islands that are very isolated, that are very far from that big area of habitat, are not more likely, they are less likely to receive migrating species. And again, even though you're not going to see a multiple choice, you're seeing a really good description of a process here that will help you understand that. So small isolated islands have a lower availability of resources. All right, let's walk through a guided practice question that kind of pulls all of the ideas together from those 4 learning targets that we looked at. So let's go back to range of tolerance. The diagram below shows the pH ranges for which selected aquatic organisms can exist. A, describe how pH affects biodiversity in a freshwater ecosystem. Let me give you a second to either think about that one or write the answer down, and then we'll talk about it. Well, this is where I can talk about how increasing or decreasing pH is going to change the diversity of that ecosystem. And notice in the responses, I could say this either increase or decrease. I could say as pH values decrease, biodiversity decreases, lower pH, lower diversity, lower number of species that can survive there. Or I could say the opposite. As pH increases, I have more species that can survive. Notice that I could also, instead of just talking about the pH value, do more an interpretation of that. So a low pH means it's more acidic. So I could state it either way. Next, explain why increasing acidity would cause a change in species composition. So here I kind of made a claim. I said what the relationship was. Now I want to explain that relationship. So I'll give you a second to think about that one. Hopefully in your either mental or written response, you talked about the idea of range of tolerance. So here's my sample response. The organisms in the freshwater ecosystem are adapted to a certain range of pH values, and when it is outside their range of tolerance, they will be less able to grow and reproduce. Therefore, I have less species present. I don't know if a pH of 4.5 is going to kill all those trout. Remember, that's kind of a misconception or a mistake students make. So if you talk about these abiotic conditions, you really just want to focus in on how they're not going to be as successful when they're outside that optimal range. Oh, let's see what else have we got here. Let's see if we can explain why the change in the pH to begin with. So explain how using coal to generate electricity can cause lake acidification. Gotta go back to your air pollution or your energy. So hopefully you remembered to say that burning coal releases SOx. Simply having a pile of coal there, remember, doesn't release any sulfur, not until I combust or burn it. So that SOx, a primary pollutant, reacts with water to form an acid precipitation that then falls on lakes and streams or runs off into lakes and streams. And one strategy to prevent acidification of aquatic ecosystems, be a little careful, because when we look at solutions, sometimes it might be kind of broad, and it could be, how do I prevent something from happening to begin with, or how do I remediate that or mitigate it? So if I didn't ask it that way this time, but the question could have said, now that the lake is acidic, what can I do to repair it or put it back to normal? So be a little careful when you're reading your FRQ prompts, when you're looking at solutions. Here I want a strategy to prevent acidification. What will cause it? Well, one thing I would do is replace coal burning with solar or wind power, because they do not release SOx like coal does. And if I don't have SOx, I can't have as much acid precipitation forming. Remember, I never want to just say don't use coal, because we need electricity. So I can replace or substitute that coal with something else. A lot of you also maybe went with the scrubbers, the wet scrubbers that could be used. They're the air pollution control device installed in the coal-fired power plant to remove those SOx emissions before they ever enter the atmosphere and thus prevent the formation of the acid rain. Okay, let's take a look at what we covered today. It was a pretty good review of that first half of Unit 2. So first we looked at the introduction to biodiversity. Take a look at my essential knowledge statements here. We looked at the levels of biodiversity. We talked about the bottleneck and the importance of genetic diversity, that ecosystems that have a large number of species are more resilient, more likely to bounce back from disruptions. Remember, we're going to look at this one a little bit more later in terms of the generalists and specialists. Oh, I took it out there. And then simply defining what species richness is. We looked at the theory of island biogeography. We defined what that is. We know that islands can be colonized with new species arriving from other places. Remember, in the broad global application of this concept, the closer those areas, those habitat islands are, the more likely they are to be colonized, and that those new species can expand. We're going to take a look at this again a little bit when we look at generalists and specialists in a couple of days as well. We looked at ecosystem services. We know that there are those different categories and that they save us money by valuing those ecosystem services. And we looked at the idea of ecological tolerance, the range of abiotic conditions over which organisms can survive. So we reviewed a pretty fair amount there. I got a great practice question for you to try, and then you'll go over this tomorrow with Dr. Sowell, just to review your task verbs. And I know Dr. Sowell addressed this a little bit. You will maybe have to look at a data set and interpret some data, but you're not going to have to perform any mathematical calculations. That was one of our 3 FRQs, and we only have the 2 this year with the modified COVID exam. We have the experimental design main focus and the solution main focus. So all of the rest of these are those task verbs that you should be familiar with. Let me introduce the question to you. Refer to the figure or diagram below to answer the question. Notice my directions. Where explanation or discussion is required, support your answer with relevant information and or specific examples. This is that sort of because, therefore. I want to keep going and make sure I've given a complete picture. This is what happens. This is identifying a process that happens. This is explaining that process. And this is then you kind of go to the why do we care? What is the broader application? How does that help me understand a bigger environmental issue? So I'm going to identify the 2 scales on which we can measure biodiversity. We're going to use the diagram to describe the difference in the biodiversity of the 2 communities. You've got different kind of species represented there. Describe a regulating ecosystem service provided by forests. And then here's where we get into a little bit more of the experimental design. An ecologist is interested in the effect that fire intensity has on biodiversity of tree communities. Describe the control group. So describe what you're going to use as your control. State it and why it's a control group. And then the diagram illustrates some of the results of the experiment. And they want you to state a likely original hypothesis based on that. So Dr. Sowell tomorrow is going to be talking about impacts, disruptions to ecosystems, and carry through that idea of biodiversity. So it should really be a nice blend in from what we talked about today. Have a fabulous rest of your Monday. Hope everybody is safe. Hang in there. We're going to be done with Unit 2 out of 7 reviewing, and you guys are doing a fabulous job. See you on Wednesday.
Hello, AP Environmental Science students. I'm Dr. Sowell, and we are going to proceed with our review of our content for the exam. I teach APES down here in Jacksonville, Florida. It's hot and swampy and wet today down here. So just as a reminder, here's our exam date, May 18th, and those are the times. And then we've also got the details of what's on the exam, the 2 FRQs that you take a look at. So yesterday, Ms. Fassler talked to you about biodiversity and really got into the theory of island biogeography. So just to review some of those concepts on biodiversity, she left you with an FRQ, and we are going to go over that together now. So the first part of your homework asked you to look at this diagram of 2 forest communities, community A and community B, and it says identify 2 different scales on which biodiversity can be measured. So it's asking for 2 different things. So it's 2 points here, and you could have said either genetics, species, habitat, or ecosystem biodiversity. Those different levels of biodiversity. So statements such as biodiversity can be measured by genetic diversity and species diversity would have gotten you both points because it's just an identify, not a describe or explain. The second part says use the diagram to describe one difference in biodiversity between community A and community B. Well, if I just look at these 2 communities, I see that there are 5 different species of trees here and 5 different species of trees here. So the species richness itself isn't that different, the number of different species, but their abundance is. And so the correct answer would be something like community B, here on the right, is more diverse than community A because B has higher species evenness than A. Or you could have said it this way, community A is less diverse because one species of tree dominates the community. The tree populations in community B, however, are more equal in terms of proportion. So that's just another way to describe the biodiversity between A and B other than they have the same amount of species. The next part C says describe one regulating service provided by a community like the one shown above. So you could have said any kind of regulating service provided by a forest, regulating climate, regulating local air quality by removing pollutants or increasing the amount of shade, storing carbon, sequestering carbon through photosynthesis, moderating extreme weather events, filter water, and there's probably a few more that aren't listed here, but any one of those regulating services for the forest ecosystem, not of a tree, but of a forest. And the last one says an ecologist is interested in the effect that fire intensity has on the biodiversity of tree communities. Describe the control group for an experiment that examined the effect of fire intensity on the biodiversity of tree communities. So if we're looking for a control group and we're studying fire intensity, well, clearly the control group is the one with no fire or no fire intensity, and that fire intensity of 0 can be used as a comparison for the baseline amount of biodiversity. And this fire is an example of a disturbance that we'll look at today. So that's worth 1 point. There's 1 more point. So it also says the diagram illustrates some of the results of the experiment. The experimental group with the highest intensity fire after 20 years is shown in A. The experimental group with the lowest intensity fire after 20 years is shown in B. Based on this information, state the likely original hypothesis. So this is 1 point. So it could have been something like high intensity fires decrease the biodiversity of tree communities or forest ecosystem, or you could have said the opposite. Low intensity fires increase those things. So we're looking for a hypothesis based on the experiment that is described. So remember, experimental design is part of your FRQ1 in some flavor. All right, so where are we going today? We're going to talk about 3 things: 2.5, 2.6, and 2.7. So Unit 2, topics 5, 6, and 7: natural disruptions, adaptations, and ecological succession. And a few times along the way, we will stop and look at practice 5 about interpreting quantitative data. All right, so let's pull back a little bit and look at our big idea. So one of the big ideas for our course is this. The Earth is one interconnected system. Natural systems change over time and space. Biogeochemical systems vary in ability to recover from disturbances. So you'll notice that change and response to change, recovery, lack of recovery, really does highlight the fact that ecosystems have structure and diversity that change over time. Our world is not a static place. There's Earth processes and systems that cause changes naturally, and organisms must adapt to them. And if they don't, they go extinct. So by the end of this first section on natural disruptions, you should be able to explain how natural disruptions, both short and long term, impact an ecosystem. And this actually will carry through the entire lesson today. But initially, we will define what a disruption is in terms of its characteristics and some of its consequences. We'll look at some examples of the natural disruptions at different scales, and then we'll look at how organisms respond to those disruptions. But again, first we got to define what we're talking about. A disruption is an event. It's an event that changes the structure and function of an ecosystem. And again, we're looking at natural disruptions here. So here's some examples: a hurricane, a forest fire, a volcanic eruption, a flood, a tsunami, a drought, a wave of insect pests. Any of these events can affect the structure and function of the ecosystem in which they happen. What we're not talking about today are anthropogenic disturbances, human-caused disturbances like tilling a field or clear-cutting a forest, burning fossil fuels to cause climate change, or maybe even fishing, like trawling the ocean floor. So today we're not going to focus too heavily on anthropogenic. We may a little bit, but for the most part, we're looking at what are the natural disruptions that just happen, short-term and long-term, to our Earth processes and systems and environments that cause organisms to have to respond to them. That's what we're looking at today. All right, so some natural disturbances can have greater impact than some anthropogenic ones. So meteor hitting the planet, causing a big loss of species like the dinosaurs. That's a big impact. That's a lot bigger impact than me clear-cutting a forest down the road. But either way, they can really have big effects on habitats. They can wipe out a habitat, or fragment it, or change the environment. Another example of a large-scale natural disturbance would be sea level rise over time. So if we look over hundreds of millions of years ago, we've seen sea level change, rise, and fall over time. Well, if you're an organism that lives in a coastal area and sea level rise happens, that's going to force you to either adapt or go extinct. So these natural changes do shape the organisms that live on the planet. And they can occur at different time frames. So our Earth systems don't all happen every Tuesday at 3 o'clock. There's an earthquake kind of thing. There are certain things that occur on a regular frequency, and some things that are more random. So if we think about a periodic change, they occur pretty much regular frequencies, like the rainy season or a dry season. That's an annual event. The frequency is pretty regular. Then we got something that's episodic that happens occasionally, but not with a regular frequency, like a hurricane. Here in Florida, we get lots of hurricanes. Some years we have more than others, but there's no particular pattern and number and timing of them that is a regular frequency. And then we have things that are more random, no particular frequency. Yeah, random doesn't mean that we don't know how they occur. We know what causes a volcano, but the eruption of that volcano or the earthquake or some of those processes don't happen on a particular regular pattern. So that's why we consider it random. All right, so let's look back at Africa. So the other day when we were reviewing terrestrial biomes, we used the HHMI Biointeractive Biome Viewer to pull up some climatograms of different locations. So let's just go back and look at the one here in Mozambique and Gorongosa in Mozambique. If we just look at temperature and precipitation, we clearly see that during the summer months, the temperature goes down and the precipitation goes down. So we clearly have this disturbance that happens in the summer months here in the southern hemisphere that organisms have to deal with. So this is a distinct seasonal change in precipitation and temperature. It's a periodic disturbance of this dry season, and it affects the structure and population of the organisms that are there. So here's a little clip of that information, especially looking at precipitation. So if you'll notice in the summer months, it starts to dip down and come back up, and you'll see that same pattern in the video here. And all I'm doing is going on the Biome Viewer under precipitation, picking that location, and then changing the months so that you can see that the rainy season and the dry season is happening. Now we're in the summer months, get back into November, December, and then the rains return. So it is a cyclical pattern there. So how might this periodic natural disruption affect the organisms that live there? Let's take a look at the wildebeest, for example. So the wildebeest migrates in response to those rains. So the seasonal rains are periodic disturbances that shape the behavior of the organisms living on the savannah. So these wildebeest migrate, and not just a couple blocks down the street. This is hundreds and hundreds of miles. This is a big migration that happens annually in response to that natural disturbance. This is just a map of a herd moving from in between Tanzania and Kenya around Serengeti National Park. But you can see that there is this annual migration that really does follow those patterns of rain. So obviously, these organisms, these wildebeest, have evolved particular adaptations that benefit this lifestyle of migration. So what are some specific adaptations? So they have a body structure for long travel. So their legs and their musculature really do benefit these long distances they have to travel. Herd movement. They don't do this alone. Safety in numbers. You know, one guy's looking out over here while the other guy's eating. So lots of eyes out for predators. That herd movement is an evolutionary adaptation that's beneficial for these long migrations. They have particular mouths and lips for grazing on these short grasses that they're following throughout their migration. And finally, another one is calves. So as soon as a young wildebeest is born, within a couple hours it can stand, and within a couple of days it can keep up with the herd. That would be an important adaptation for the success of a migration. So how do these adaptations get there in the first place? That's the topic 6 for Unit 2, describing how organisms adapt to their environment. Now clearly we're talking about evolution here. Now for the AP Environmental Science course, you need to understand the basic mechanisms of evolution. We don't go into it as much detail as say AP Bio would. So to get to this ability, we are going to explain the connection between these environmental changes, like these disruptions or disturbances, on organism survival, and then we're going to explain in general, very briefly, the mechanisms of that adaptation. So going back to our big idea, remember change is constant. Change is always happening, and that these disruptions and disturbances are normal. We have natural disruptions and disturbances that occur. And then we could say that they're seasonal, short-term things like the rainfall disturbance, or these big long-term disruptions like sea level rise. But again, like I said before, organisms must, over time, adapt to living with these changes or see you later. So clearly this is coming on a genetic level. So we're looking at DNA here. That is the basis for these adaptations. And so we have our DNA. We're all familiar with that. And then every once in a while, there's a random mutation. And again, that is a random event, a change in the DNA. Sometimes the results of that are positive, sometimes the results of that are negative. But the mutation itself has no value until the environment in which the organism lives in decides whether that mutation and the resulting phenotype is beneficial to the organism. So the mutations are random, natural selection is not. So what do we mean by that? Well, these wildebeest all have these adaptations that help them to migrate. And if those adaptations didn't occur, the species as a whole wouldn't survive. So they've had lots of random mutations within the population of wildebeest. But those mutations that provided a benefit for the organism to deal with this migration were kept and favored. And those individuals were more likely to survive, reproduce, and pass on those genes to the next generation. So we're going to move away from the wildebeest a little bit and look at another animal, the rock pocket mouse. And so this is taking place in the desert southwest in the US. And if you'll notice here, what you would expect, a desert would have light, sandy substrate on the desert. Then we've got these little rock pocket mice, and they have a unique mutation. They have mutations that will affect their fur color. Some have darker fur and some have lighter fur. And if we stop right there, those genetic mutations have no value whatsoever, either good or bad. It's only when their environmental conditions, maybe even a disruption, selects which one might be favorable. So the population as a whole can change if that selection selects for certain mutations. So we're going to take a couple minutes of a little clip here, about 3 minutes, to go over these rock pocket mice.
Across the American Southwest, golden deserts dotted by cacti and brush stretch for miles. Yet here in New Mexico's Valley of Fire, the landscape changes dramatically. Patches of black rock interrupt the sand, remnants of volcanic eruptions that occurred about 1,000 years ago. The eruption spewed a river of lava more than 40 miles long across the desert. As the molten rock cooled, it darkened, leaving any creature dependent on camouflage in serious trouble. In the complex battle of life, one of the constant struggles is being seen and not being seen, the evolution of game of hide and seek. And we've come here to the Valley of Fire in New Mexico, a battlefield, to find one of the tiniest soldiers and what it can teach us about how evolution works. On the desert sands, the rock pocket mouse blends in perfectly. Its light-colored fur is sealing it for predators. But on dark lava, the same fur makes the mouse stand out, attracting the many creatures that see it as food.
These mice are the stickers part of the desert. They're eaten by foxes and coyotes and rattlesnakes and certainly by owls and maybe even occasionally hawks, and most of those predators are visual predators.
So what happened to the pocket mice that found themselves on this new terrain? My accompanying biologist Michael knocked them onto the lava. It doesn't take long to find out. Oh, this one's closed. The Doctor has been collecting mice unharmed in traps. And it's a dark one. It is, yeah. Now, are most of the ones you find up here dark? Almost all. Not only have the mice here evolved to be as dark as the rock, the color change has occurred precisely where it will conceal them from hunters.
No, they have a white underbelly too. That's right. All of the dark ones here and a lot of those have a white underbelly, and presumably there's no selection for dark on the belly because predators are coming to love.
Left to themselves, the mice show no preference for light or dark rocks. It's the predators that have made the difference.
The change in color over evolutionary time of the population is driven by predators weeding out the mice that don't match their background.
So pretty cool story, a great illustration of adaptation and evolution. So if we kind of look at a visual representation of what we just talked about, let's imagine this is a location where there's no volcano, there's no lava flow. And in this situation, the numbers of light and dark mice pretty much stay even. There's rarely a lot of dark mice because that particular mutation results in them being hunted more often. So when there's no volcano, population kind of stays the same. But if we look at a situation where we have a volcano, and then all of a sudden we can see population start to change. The number of light mice decrease and the number of darker furred mice increase. So we can clearly see the effect of that disruption on the ecosystem. Now, one of the things you may be asked to do on an FRQ is to explain patterns and trends in data to draw conclusions. So we've seen this story in a video version, you've seen it in a little picture version on the last slide, but we can also talk about this in terms of a graph. So could you stare at this graph and tell the same conclusion? Now, what we can do is we can look at location A, which is the first two bars of each graph, and really location A really doesn't change too much in terms of the proportion of light and dark fur. But if we look at location B, we see the number of light fur decreasing and the number of dark furs increasing. So that is just another visual representation, quantifiable representation of the same story. All right, so let's look at one more example of this adaptation where an organism is evolving to adapt to a disturbance. Now, this particular one we're going to look at is an anthropogenic disturbance. It's adding antibiotics to bacteria. And so even though we're studying natural disruptions today, I want to point this out because this particular piece of content will come in handy when we think about antibiotic resistance within a CAFO, for example, or perhaps what's going on underlying the pesticide treadmill when we get to agriculture. So similar stories here. So this is a really fascinating experiment where they took a petri dish. So a petri dish is normally about this big. They made a giant petri dish, a mega plate, and they grew some bacteria in there. But what they did is along the way, they would increase the amount of antibiotics, and antibiotics would typically kill the vast majority of the bacteria. But every once in a while, there was a mutation that allowed them to survive, and they flourished. So this is a great visual of that process. So here they're filling up the plate. And this is just the growth medium, what the bacteria grows on. And they added in some antibiotics at different concentrations. So if you notice here in this first section on the left and the right, there's no antibiotics. So we should see the bacteria population really thrive here as it grows toward the middle. But then here we should see a big stop because now we've added some antibiotics. So we should see the majority of the population stop right here. But what you'll see is they will evolve as they move towards the middle. And this is happening so quickly in 11 days because this species reproduces so quickly. Bacteria can reproduce in a very fast rate. So you're going to see a change in their population in much quicker time than you would in the mouse or even something like an elephant. It's going to take a lot longer to reproduce. All right, so increasing concentrations of antibiotics as we move to the middle. You can see they stop at the border where the antibiotic starts. But and those are the bacteria that have the adaptation for living in higher and higher and higher concentrations of the antibiotic. So if we stop here, this is the same species as this. It's the same organism. It is simply adapted and evolved over these 11 days to resist this level of antibiotic. Pretty cool. All right, so excuse me, what you can see here is whether we're talking about mice or bacteria or maybe even the scrub jay, which is a species under threat here in Florida, that our goal is to have a healthy big population so that the genetic variation is maximized. We want the maximum number of genetic possibilities within a population. So that means maintaining a large, healthy habitat so that the populations don't get too small. If they get too small and the gene pool gets too small, they're more at risk of extinction. All right, so now we're going to go to the third topic of this unit, which is ecological succession. Still under the umbrella of change over time, but now we're going to look at how a single community changes over time. So to get there, we're going to define succession. There's two types of succession we need to delineate: primary and secondary. Then we're going to look at pioneer species and their role in primary succession. That's a cool story. I like that. We'll look at the effects of succession. How does that change an ecosystem? Then we're going to look at two particular labels of species. One is a keystone species, and they have a very unique role in an ecosystem. And then we're going to look at an indicator species. That's something that we use in experimental work for a very particular purpose, so it has a utility for us. So that's where we're going. All right, so again, ecosystems have structure and diversity that change over time. So if we look at this forest community, it is not static. It changes over time. If we look at this field down here, just little annual plants, over the course of decades, maybe hundreds of years, it becomes a forest. And that process is called succession. So succession is the sequence of changes in a community over time. Now, like I said before, we do delineate between primary and secondary succession. And really the distinction is quite simple. Primary succession happens when there's no soil. And that's a pretty rare event in terms of kind of wiping out the surface of the earth where there's no soil. Typically we see it from things like the volcanic eruption we saw before. That would kind of wipe out all the soil. Or a glacier retreating, that would scrape away the soil. So when that area, that community of no soil is building up, that's primary succession. If there's soil already there, that's secondary succession. So if I'm interested in seeing how this community of perennial herbs and grasses is becoming a shade-tolerant tree-dominated forest, that's secondary succession. A good example of secondary succession is a forest fire. This is a longleaf pine forest from down here in the southeast, and we can see that this fire, which is natural, this is a natural disruption, has kind of cleaned out all the understory, the herbaceous grasses that existed on the understory, but they're starting to come back, and then they reestablish themselves here. So this process of changing the community over time is called succession. So that makes sense. The soil's still there, so the plants can simply regrow back on the soil once the seeds or the spores land there. But what if we have a place where there is no soil, like that lava flow? So we've got a volcano, we've got some lava, it starts to ooze out everywhere, flow everywhere. What we're left with? Zero soil. Well, if an oak tree seed lands on that lava field, it cannot grow. There's no soil there. There's not enough nutrients or soil or anything for it to get going. So how do we even start this process? So before we go into the details, I do want to point to a great place to practice this. This is the 2014 FRQ about the Ring of Fire and plate tectonics and tsunamis. But part of that really lends itself to what we're talking about today. It says, although the landscape following a volcanic eruption may appear unable to support ecological communities, over time, the area can be transformed through succession. The first part says, what's primary succession? And the second part says, explain how primary succession can lead to soil formation. So exactly what we're going to talk about today. So primary succession, like we said, is the establishment of organisms or a new community where no soil previously existed. And B, or my eye, talking about how we get soil, that is where we see organisms weathering the rock and decomposing to add nutrients. So let's go into a little bit more detail about that process. So if we look at this early successional habitat, so this is one community changing over time. Back here in the early stages, what kind of organisms might be most suited to live here? Clearly not a deer, clearly not even an earthworm. There's no soil there for the earthworm to live in. There's no plants for the deer to eat. So what we're looking at are a group of organisms called pioneer species. And these pioneer species are things like lichen, bacteria, and mosses, and they're the first ones to arrive. Now, this is a harsh landscape. There's not a lot of resources there. So these organisms have had to evolve particular reproductive and life strategies to allow them to live in these conditions. One aspect of their life is their reproductive strategies, which is in this case is an R species or an R selected species. And we'll talk about more R and K species when we get to populations. But these R species, one of their characteristics is they have a huge reproduction rate with low parental care. So if I'm a fern, I can distribute millions of spores and peace out spore, good luck. As opposed to mother elephant that might care for her elephant for a long time. But anyway, that's a different story. What we're looking at today are these pioneer species, these ones that kind of take this rugged environment. So one of the unique things that some of them can do, like the lichens, is secrete an acid that starts to weather down the rock. And when we get to soil, we'll talk a lot more about this. But soil is one of those beautiful places where the lithosphere meets the biosphere. It's like this recipe that is made from rocky stuff and living stuff. Well, these lichens kind of get the recipe going. They break down the rock into smaller and smaller and smaller pieces, or at least get the process started. But that lichen or that moss or that fern is eventually going to die. And when they die, they decompose and their organic matter gets mixed in with that weathered rock. Boom, now we've got some soil. Not a lot of soil. Can't grow an oak tree yet. But we've got a little tiny bit of soil, broken up rock with some decomposed organic material. That now can maybe support a little large plant. And then that plant dies. Maybe supports a large plant, maybe a spider. Well, when those things die. So you can see that over time the soil gets bigger and bigger and bigger, and we can support more and more life. All right, so here's a picture of this. So we start over here with just bare rock, and over time we get to this forest community that has a really biodiverse, species-rich ecosystem. So the succession of plant communities above the ground is kind of mirrored by the soil development below the ground. We can see the soil going from non-existent to all of these horizons of very rich and developed mature soil profile. So over time we can see changes in biomass. Clearly there's much more living stuff in late successional communities. Species richness, vastly different from what we saw here in primary succession. And then NPP, think about that. Think about the difference between NPP of a bare rocky area, almost like a tundra or a desert, versus a tropical rainforest or something that's here. So I'm not saying the deserts become tropical rainforest, but I'm saying over time, as a community goes through succession, its NPP changes, its productivity changes. So I want you to imagine now, what if I took away this fern? What if I took away all the ferns from that community, that late succession community? Would it affect the community? Absolutely. The things that ate the ferns might decrease. Maybe the nutrients in the soil might shift because the ferns aren't drawing that out. But by removing the ferns, or if I remove the mold, or if I remove the fungi, the forest is still staying a forest. However, there are some organisms that, if they are removed, completely changes the successional pathway of a community, and that community can become a completely different one. So what I'm saying here is not all species are equal in terms of how community functions. Some you can take out and it might shift the food web or change the food web or soil dynamics, or it might change something. But there's others that if you take it away, the whole ecosystem changes, the whole community changes. And that's what we're going to look at through the famous work of Dr. Robert Payne, brilliant scientist who was really famous for this first experiment he did with starfish, talking about the role of keystone species. So he investigated tide pool communities, and he studied how the removal of this one species of large starfish would affect the rest of the community in the tide pool. Again, an extremely important experiment in ecology. So he was really interested to see how these kind of apex predators like these starfish regulated the biodiversity of an ecosystem. So one way to do that is to kind of make an experiment where he removes some, and you'll see how he did that here in this lab. We're going to watch just 2 or 3 minutes of this.
He began by identifying all the organisms, and then he started mapping out who eats whom.
There were carnivorous gastropods feeding on barnacles. There were sea urchins feeding on algae. There was a lot of pattern.
His observations showed that a species of large purple and orange starfish called Pisasterocratius was at the top of the food chain. Starfish may seem like unlikely predators, but speed time up a bit and you'll see deadly hunters.
If the starfish is feeding, you turn over and you see what the starfish is eating. They're eating mussels. They're eating a lot of other things as well, but they're eating mussels.
So Payne asked, what happens when you remove the predator starfish from a single outcrop?
You have to surprise them because the starfish clamps down. It takes a strong wrist and a pry bar. I would then scale them as far as I could. And in those days, I could throw starfish 60 or 70 feet out in deeper water. There were always starfish marching in, so during the summer months, I would drive the 350 mile round trip, hit the area at low tide, do my removal, take other data, and then return to Seattle.
The ecosystem started to change rapidly.
Within a year and a half, I knew that I hit ecological goal.
Although the top predator had been removed, surprisingly, the number of species in the rock actually decreased.
So that's a little different than what we would expect. You would think if you took away this top predator, that the other species below would be like, oh, thank goodness, the predator's gone, and the biodiversity would increase. He saw exactly the opposite, and here's why.
From 15 to 8.
After 3 years, it went down to 7, but then by 7 years, it simplified itself till it was basically a monoculture. I changed the nature of the system.
As the experiment continued, the line of mussels advanced down the rock face, monopolizing almost all of the available space and pushing all other species out. Payne had discovered that one predator could regulate the composition of an entire community. He coined a term to describe the power a single species can exert on an ecosystem.
I know very little about architecture, but if you build an arch, you have to get the 2 sides of it to put pressure against one another. And therefore, at the apex of the arch, you have a keystone. You pull the keystone out, and the structure collapses.
So very cool study that he did. So again, Robert Payne's work on keystone species is very, very important in understanding succession. So this species has a crucial role in maintaining the community structure. It affects lots of other species in that community, can really drastically reduce the biodiversity of an area. This is a unique characteristic of a keystone. Typically, it's not the most abundant species. Therefore, the impact it has on the community is much greater than you would think because of its low abundance. But its absence would affect the entire structure or functioning of the community and kind of alters that successional pathway. So we see here that early, before he went and removed the starfish, had lots of biodiversity. After removing the starfish for a year, it started to go down. 5 years later, the species richness was reduced to 1. So we saw this one organism not just affecting the things that it eats and what is eaten by it, but the entire rest of the trophic levels. We call that effect a trophic cascade because its effects cascade down to other parts of the food web. So another good example of that is an African elephant. So one of the things an African elephant will do as it eats vegetation is strip trees down, knock trees over, trample them, and it really reduces the amount of forest. This actually keeps the African savanna a savanna. If you removed the elephants, then the ecosystem would actually go through a different successional pathway and become a forest. So you can see that this one species, not a very abundant species, has the ability to shape the entire structure or function of communities. Another famous example is with wolves. So over here on the left-hand side, this is before the wolves were removed. So we have a large mix of small and large predators. There's a diverse plant community, lots of birds, few large herbivores. But once those top carnivores are removed, the smaller predators dominate. And so what we have is a big explosion of these herbivores, which reduce the plant community, plant biomass, and therefore reduce some of the songbird diversity. biodiversity. So again, one organism, the wolf, having this cascade effect all throughout the community, this trophic cascade. All right, so the last type of organism we're going to look at is an indicator species. And this is a species that we define as a useful way to count and understand the health and stability of an ecosystem. So let's take this wood stork over here at the top right. This is a common bird in the Everglades, or in kind of marshy wetlands here in Florida. And so one of its habitat requirements is in order to feed, it needs shallow, rather turbid, seasonal pools of water in which fish are concentrated. And what the bird does, it'll open its beak and kind of wade its beak through the water with the beak open. And as soon as it feels a fish, it'll slam shut. Well, that ability, that adaptation can only occur in shallow, turbid, seasonal pools where fish congregate. And that's a natural state of marshland like the Everglades. So therefore, if I go out to the Everglades and I see lots of wood storks, that's an indicator that the ecosystem is doing well. But if I go out there one season and the numbers of indicators, the numbers of wood storks have gone down dramatically, that means that something is up and I need to look further, indicate something is amiss. Now, I picked the wood stork as my indicator species because it has a very specific habitat requirement that really defines the ecosystem. Here's an example of what you would not pick. A raccoon. A raccoon could easily live in that salt marsh, but it could easily live in my neighborhood by eating trash out of the trash can. So that kind of generalist species that isn't really connected intimately to one ecosystem would not be a good species to call out for indicator. And then down here at the bottom, lichen. Lichen is a famous indicator species for air quality. So overall, an organism whose presence, absence, or abundance reflects a specific environmental condition. In this case, shallow, turbid, seasonal pools. In this case, good air quality. Again, it gives us an overall indication of the health of the equilibrium of an ecosystem. And it's usually an organism that you could count or quantify pretty easily. You wouldn't want something that is almost hard to detect. Finally, a nice one to think about is amphibians, such as frogs, because of their intimate relationship with aquatic environments. They're a great indicator species for water quality. That's often used. All right, so let's do a quick check for understanding. Again, I'm going to give you some quantitative data in the form of a graph to understand and ask you a particular question. All right, so the question says the data on the left represents the normal biodiversity of a community. The extinction of the crab, a keystone species in this community, would most likely result in which of the following? So take 30 seconds for that question. So the answer here would be an increase in algae biomass, because the removal of this crab would cause a population explosion in this fish, which would cause a very low population of these organisms, and therefore the algae would increase. So this is a good example of a trophic cascade, where the abundance or absence of one organism has a very big effect on the rest of the community. All right, so where did we go today? We looked at disruptions, natural disruptions, adaptations, how organisms evolve to adapt to those changes, and then we saw ecological succession, how a community itself changes over time from primary to secondary succession, and how certain species like the keystone and indicator species are useful for us to understand those areas. Just as an aside, to think about conservation strategies, if you only had $5 to spend to save one species, maybe you save the keystone species because that does have such a large influence on the ecosystem. So what am I going to leave you with tonight? Another FRQ for practice. So again, pay attention to the task verbs, and this is the question that you're going to be answering for homework. And Ms. Fassler will talk about this tomorrow. This starts out with content that we have not got to yet in the review, generation of electricity, a hydroelectric dam. But you covered that content in class before, hopefully, so that part will be a review. But towards the end, it talks about keystone species and the roles beavers play in those ecosystems. So this is the FRQ I will leave you for next time. And again, please reach out if you have any problems with connectivity or the mobile tools that you're going to need for this course or for the exam coming up, or if you know anybody else who might, please use that URL below. And again, thank you guys so much for doing this and sitting here and listening to me ramble on and on. Ms. Fassler and I are so thrilled that we can be doing this for you guys. Hopefully it's beneficial to you. And I'll see you next time. Bye.
Hi, welcome back to our AP Environmental Science virtual class in the classroom. I'm really glad you guys could join us again today. I'm Ms. Fassler. I teach APES at Marshfield High School in Marshfield, Wisconsin. If you want to get the homework that you did with Dr. Sowell yesterday, we're going to start by taking a look at that. What an exciting lecture you had. We actually finished up Unit 2 for review yesterday by looking at more in detail about biodiversity and how disruptions, both natural and anthropogenic, can lead to changes in ecosystem, changes in biodiversity. And you left off with ecological succession and did some work with keystone species. So as Dr. Sowell mentioned yesterday, the question that you looked at draws in from some other topics that we've looked at throughout the year, and we'll eventually get down to that keystone species. But super good practice in letter 8 here for explaining how electricity is generated by a hydroelectric dam. So remember when I explained how something happens, I'm describing a process. This was a 3-pointed response for letter A, and they wanted to see, although the verbiage or way that I said it could vary a little bit, I had to have 3 steps that basically converted potential to kinetic energy. I had to have moving water coming into my dam system. I had to have 1 step that can explain or describe the conversion of kinetic to mechanical energy, turning the turbine, and I had to have 1 step that explained the conversion of mechanical energy to electrical energy. Those turbines converted, that rotation of that turbine actually converted that mechanical energy into the production of electricity. In the next step, part B, boy, is this ever a really good example of why you have to take your time, step back, and really read that question carefully. There's a couple things I want you to focus on in the reading of this prompt. First of all, my task verb is identify. I don't need any elaboration or explanation. You're wasting your time. You're not going to get any point for it. All you need to do is simply state, here are 2. Notice that that's even in capital letters to prompt you, that the reader can only score the first 2 responses that you identify. And the logic behind that is that we don't want students just throwing out all kinds of answers in the hope that eventually they get one that is correct. And that really doesn't demonstrate a high enough level of knowledge. So identify 2. And the other big thing I want you to focus on is the economic benefit. When I'm reading this question in a hurry, it's really easy for me to confuse the word economic with ecological. So the next thing is that they've already kind of eliminated a couple of very obvious answers. I can't talk about generating electricity from the hydroelectric dam, and I can't have any economic factor associated with preventing downstream flooding. So when I look at those possible options, a lot of them really focus around the recreation opportunities surrounding the large reservoir that's created when we dam a river ecosystem. Then you can see some of those other options. So let's just take a step back and just quickly review what's going on with the dam so that those next couple of responses we look at will make a little bit more sense to you. So this is a really cool Google Earth image of Hoover Dam. Remember that my dam is taking the Colorado River, in this case, the natural flow of that river, and putting this very large cement structure there that's holding back all the water. This is that potential energy that's going to go through the intakes, all the working part of the dam that's generating the electricity down here. So think that those dams may have been in place there for decades. And obviously we're really changing the natural ecosystem. So that's where we're going next. Describe an ecological benefit of seasonal flooding of the floodplain of a free-flowing river. So this is one of the disadvantages of building a dam, is that I'm altering the natural habitat of that free-flowing river. And the floodplain is all that area that when the snow melts and the heavy rains in the spring, that river will naturally overflow its bank and there will be deposition of sediment. So an ecological benefit of that seasonal flooding, a lot of that again has to do with that natural process of flooding. And all of the sediment that was on the bottom of that riverbed is mixed in with that churning water when that heavy rain is running off and the level of that river is rising and rising. All of that sediment on the bottom. And remember, anything that died in that river fell to the bottom of the river. river and decompose, and its nutrients were biogeochemically cycled, and all of those nutrients are in that sediment. So that churning sediment is deposited when that river overflows its bank. Other things about the sediment can then reestablish any stream banks that have been eroded, and a lot of times this is really important habitat for some of those river species that might go into that shady bank area to hide from predators. And then again, you can kind of see a few other examples there. I think a lot of people kind of went with something about the fertility of the soil when that nutrient-rich sediment was deposited. So then we go into removing dams from river, undamming the river. Some dams have been removed from rivers. Explain how the removal of a dam can benefit a fish population. Oh, that's right. When we put that dam in there, we really alter habitat. So I think a lot of people went with the idea of restoring the habitat. And again, how important your verbs are here. When I remove that dam, I put the habitat back to the way it was. And a good way to say that is simply to repair that. Remember that this riparian habitat, that refers to the areas along the banks of a stream that have vegetation and again, provide shade and shelter for fish populations. Many of you may have talked about fish that migrate or swim upstream for mating, and that the dam presents a barrier that prevents them from doing that. And again, we can change a lot of these abiotic conditions as well during the restoration. I think this next question was one of the most challenging questions in this FRQ, is it was to describe one negative environmental consequence of the removal of a dam. And I just think that's something maybe we don't think about a lot, but realize that if that dam has been there for decades, it's going to, first of all, have to be careful how we remove it, because I have a massive amount of water stored behind that dam that all of a sudden is going to inundate my downstream habitat. All of that sediment, that important nutrient-rich sediment that we've been talking about, has been held behind the dam. Remember, I don't have that natural flooding process. When I store that water in a reservoir, there could be even harmful substances or pollutants that have accumulated in that sediment that now all of a sudden I'm releasing them and increasing that concentration downstream. Maybe invasive species that have been caught behind the dam. So the bottom line is that it's going to take a while. Restoring that ecosystem to its natural ecosystem is wonderful, but there are it's a little bit of a process to get that done, and we have to make sure it's done correctly. And that was where you got into the real strong application to your great lecture from yesterday on how beavers act as keystone species. Remember that keystone species is that one that holds up or supports many other populations within that ecosystem, and beavers can alter habitat by making a dam just like a natural dam does, but understand on a very small scale. I mean, there's a beaver that builds some pretty big dams, but for the most part, they're creating in a small river or stream ecosystem, they're creating little ponds. They're creating habitat for other organisms that might live there. And then again, you could have talked about sediment and stream back erosion and things like that. So great question from yesterday. Let's take a look at where we're going today. You've seen this slide a number of times and will probably for, I think we have about 10 or 11 lessons left. Just to remind you about your exam date, that we're testing on the first 7 units. And just to be clear, if your teacher maybe did a slightly different order, when we talk about 7 units, Dr. Sowell and I are systematically going through every learning target, units 1 through 7. So you are going to get a review of all of the content that you're going to see on the exam. Today, we're really going to live within this part of the skills or processes that are used on both of our FRQs. We're going to look at a lot of models and representations of quantitative data and analyze those to explain or describe environmental concepts and processes. So the content that we're looking at today, we're starting in on unit 3 on populations. And remember that populations within ecosystems change over time in response to a variety of factors. So we're still going to kind of live within this big idea that the Earth is one big interconnected system. We have 2 lessons within unit 3 on population. So today I'm going to cover the first half of it, reviewing the basic population ecology. And tomorrow Dr. Sowell will finish up with unit 3 by looking at human population. But again, our overarching theme throughout this unit is to look at data and look for patterns and trends that we can use to understand and explain environmental processes. So we've got 5 pretty straightforward topics here that all really integrate together, looking at what generalists and specialists are, how that relates to them, to their reproductive strategy, and then we'll get into that population curve and look at resource availability and how that influences populations. Just to remember, you do not have to do any mathematical calculations, although you will look at data represented graphically. There won't be any manipulating of that data with your calculator. It's good news for a lot of people. So let's just jump right in with a quick review of these reproductive strategies, an R-selected species versus a K-selected species. So we're going to go really quick here. You're ready to jump right in with your answer, yell it out. I've got a characteristic here and then each extreme of that. So let's get started. Tend to be small. Would that be an R-strategist or R-selected species or K-selected species? Small tend to be R, large tend to be K. Number of offspring, few versus many, or a large number of offspring. Live in disturbed or stable environments. Disturbed R-selected, more stable K-selected. The amount of energy they expend per offspring. A significant amount of energy, K-selected, little amount of energy, small amount, R-selected. Mature early or late in life. A lot of these are kind of tying together with the term we'll look at here in a second. Their life expectancy, R-selected have a short life expectancy, K live much longer. Competition for resources in their habitat. High amount of competition, probably those specialists, those K-selected, and R low competition. And finally, how is their population regulated by density dependent or independent factors? And don't worry, we're going to come back and review that if you're not sure what that idea is, what that idea is asking about. K-selected, their population is more controlled by density dependent, and R-selected independent. So just a term that does appear in our curriculum, who knows if you're going to see it on the exam, but it is a term you could use, the term fecundity. And it in general takes into account all of these things that describe an R or K-selected species reproductive potential. Do they produce a large or small amount of offspring? Do they reach reproductive maturity quickly in life, because then they can reproduce a lot more? Do they have many litters per year? All of those kind of reproductive characteristics in general, that term that describes those is their fecundity. So I'm going to take a step back for a minute, because we made it sound like all of those characteristics we looked at were super black and white, like, oh, if this organism does this, then it's K-selected or it's R-selected. And it really is more of a continuous spectrum. Most organisms don't fit that neatly into a little box of K or R-selected. And a really good example of that is a sea turtle. They're very large animals. They live a long lifespan, but yeah, they walk up onto the beach often at night. They lay a bunch of eggs and they go back into the water and hope that some of those eggs aren't eaten by predators, and that those little baby sea turtles survive. So let's take all of that content that we just reviewed about K and R-selected reproductive strategies and dig a little deeper by relating that to their survivorship curve. This should look familiar to you, where on this diagram, I am plotting the relationship between the age of the individuals and how many survive. So for example, in a type 1 survivorship, a late loss survivorship curve, I see that most of my organisms look throughout all of their age as I go across their age or lifespan from babies to adults, they don't seem to be having a large drop off in their population. They have a high survival rate. In fact, the majority of their population lives till adulthood and gets into old age and drops off. They're probably dying of old age. On the opposite end of the spectrum, we have this type 3 survival, this early loss. In other words, most of these, notice that they start off with a very high population, but really quickly the number of individuals that survives drops off. And that by the time they're halfway through their lifespan, there's very few of them left. Very few of them live to old age. So let's see if we can relate that to our R and K selected reproductive strategies. Identify the survivorship curve that's characteristic of an R selected species. And now the trickier part, make sure you can explain why. This is where you're going to use your knowledge to not just say, well, it's type 1, 2, or 3. Why is it type 1, 2, or 3? So I'll give you just a second to look at that. And I think that you probably remember that type 3 survivorship curve would be representative of an R selective because they provide little or no parental care. Therefore, their offspring have a very low chance of survival. On the opposite end of the spectrum, then, we would look at a K selected species, identify the type of survivorship curve that they would display, and explain why. And a K selected species would exhibit a type 1 survivorship curve. They provide a lot of parental care for their young. Therefore, their young are going to survive later in life, survive to adulthood, and pass on all those traits that make them successful. So the next thing we want to look at is why are they called R and K selected? And we're going to transition into looking at their growth models. So we know a lot about their fecundity. We know about them being kind of generalist or specialist species, and we can relate that to their survivorship curve. Well, where does the term R and K selected come from? Those terms really describe the population growth method of these two general categories of organisms. So R stands for the high growth rate displayed by R selected species. Notice that I have very generic labels of time and population size with no numbers, so that I can take this basic population growth model and use it to understand both an R selected or a K selected species. So these R selected have a high growth rate. In a very short period of time, their population size has gotten really high, whereas a K selected species, they start off, their population kind of starts off slow. They don't have a very high rate, growth rate. And then once they reach the carrying capacity, they tend to hover just a little bit above, a little bit below. They don't tend to have these wild, really sharp increases and sharp decreases in their population. The carrying capacity is referred to by the letter K, and that's where the K and K strategist comes from. That K comes from a German word meaning, I'm not going to say it, meaning like limit or capacity, but that's K or carrying capacity. So I think we're going to take a minute and review that idea of carrying capacity so we can make sure and put this all together. There's obviously something that limits the growth, whether I'm an R selected or K selected species. I did just keep going and going and going. Even though R selected had much wilder swings in their population, there was still something that limited the upper level of that population and made it come back down. That is the carrying capacity. It's the maximum size of a population that the environment can sustain because of resource availability. That's kind of obvious. So what's often confusing to students then is the biotic potential. So let's put these two terms together. This graph, again, very generic axis of time and population size so that I can use it to understand both R and K selected species. My biotic potential is the maximum rate a population could grow under ideal conditions in nirvana. So if I'm an R strategist, I have a high biotic potential. I'm going to reproduce and lay tons of eggs, and I'm going to do that 4 times a year. I basically am born and reproduce, and that's my mission in life, is to get those traits passed on to the next generation. So if there were nothing limiting me, my population would keep going and going. But we know that eventually my ability to reproduce hits these resistance factors. There's things that are pushing down and preventing that population from keep growing. The intersect of those two things is my carrying capacity. What amount of resources are available in the environment? How many individuals can my environment actually support? I might have the ability to keep reproducing, but the environment can't support that. So you probably remember looking at some of these resistance factors. So we're going to take this idea of things that hold down or prevent populations from keep growing at their biotic potential and determine if they're density dependent or independent. So by that we mean, does this environmental resistance factor have an influence based on the starting size of the population? Let's go through a couple examples and I think you'll remember. So competition for resources, things like food and space and mates, that is density dependent. If I have 1 individual or 10 individuals in my population, they're not going to be that much competition. 100 individuals in my population and there's much more competition for those resources. So competition for resources limits the size of my population and it's dependent on how many individuals are in my population to begin with. The larger my population, the greater the role or impact of competition. What about disease? It's kind of timely because we're doing a lot of social distancing and reducing our population density because disease is also a density dependent resistance factor. If I have, we talked about white-nose bat syndrome. So the more bats I have in the population, the more dense my bat population, the more readily a disease, a pathogen can spread from one individual to another. Well, what about a forest fire? Let's talk about some little chipmunks that might be living in my forest. And I have one area that has 10 chipmunks and one area that has 100 chipmunks. It doesn't really matter if what the starting size of my population is. That forest fire is going to limit or hold back the size of my population independent on how many individuals are there to begin with. And then we have 2 more that I'll let you try on your own. Predation, density dependent or independent. That's obviously dependent as well. And a natural disaster like an earthquake or flood, independent. Anything that like this forest fire or this natural disaster, one of those disruptions that is going to kill a lot of individuals in that population regardless of the starting size. So the bottom line, when resources needed for a population to grow are abundant, the growth rate is going to accelerate. And when those resources are in short supply, that growth rate is going to slow. This is a really interesting idea we're going to dig into in a little bit more detail in just a minute. So let's go through a guided practice together. I want you to be able to take all of this content that we've learned about R and K selected species and their population growth rates and see if we can explain a broader environmental issue. Why is it, or explain why, an R selected species tends to be an invasive species, whereas a K selected species, they tend to be endangered species, or endangered species tend to be K selected. Well, one of the first things I can talk about is fecundity. So let me kind of model for you how you would say this. I could say that R selected species tend to be an invasive species, or invasive species tend to be R selected species because they have a high reproduction rate. So when they invade or move into an area, they quickly outnumber many of the native species there because of their high reproductive potential. Whereas endangered species tend to be K selected because they have a low fecundity. If there is a disturbance in their environment, it's going to be very hard for them to rebound or rebuild their population because they reproduce in such low numbers. R selected species are resource use generalists. They don't really have a very specific type of food that they eat, or maybe they don't have very specific nutrient requirements. They can take advantage of a disturbed area. So here's a picture of kudzu, an invasive plant species that most of us have probably studied that is very much a generalist. It was initially planted to, I think, to curtail erosion and hold an anchor soil in place because it doesn't have a lot of specific soil requirements and could grow really easily in a new environment that it was introduced in. Endangered species, on the other hand, as a K-selected species, tend to be resource use specialists. Panda bear will eat bamboo, and if they don't have bamboo and there's disturbance to their habitat that alters their food supply, they usually don't have a backup plan to go to. The invasive species take advantage of disturbed areas, whereas endangered species tend to like intact habitat. We're kind of out of whack there. Endangered species like to prefer intact habitat, whereas if I'm an invasive species, it's really easy for me if there's some type of disturbance, I can get in there and get foothold and take hold before those native species have an opportunity to repopulate. So let's take a look at some population cycles now. And I want to point out to you this essential knowledge statement. This is really what we're digging into here. That the resource base as a resource base of a population shrinks, the increased potential for unequal distribution of resources will result in increased mortality, decreased fecundity, or both, resulting in population growth declining to or below carrying capacity. capacity. So there's just a lot going on here, but I think one good way to illustrate that is to go back to the sort of classic ecological case study of Canada lynx and snowshoe hare and the cyclic nature of their populations of this predator, the lynx, and the prey species, the snowshoe hare. We have really good records because these were both animals that were hunted and sold during fur trading. So we have really good records about how many pelts were being caught and sold so that we could estimate population going back quite a ways. And obviously there's a cyclic nature here. As the predators reach a peak level, the hare tends to react. And initially when we see this, we say, oh, we can explain this because when there's a large population of lynx, then they're going to eat all the snowshoe hare. And so the snowshoe hare population is going to go down. And then when if there's not very many snowshoe hare, the lynx aren't going to have as much to eat, so their population is going to go down. And there's this cyclic nature of it. But it's actually a pretty interesting story. There's a little bit more to it, and it has to do with this decreased fecundity, part of this essential knowledge statement. So these rabbits, the snowshoe hare, have adapted this amazing ability. They're kind of controlling this whole situation. When there's a large lynx population, they kind of say, I'll show you guys, we're just not going to reproduce as much. We're not going to make as much food for you. So instead of 4 litters per year, they might have only 2. Instead of 20 little baby kittens or kits per litter, they're only going to have 7 or 8. So they have this amazing adaptation that they pass on from generation to generation. They maintain their populations just long enough for the long-term survival without starving out their predator. And the lynx, as a specialist, has few other dietary options. They're in this Arctic environment where they have really this specialized niche of eating snowshoe hare. And if those snowshoe hare aren't reproducing as much, if they purposely lower their fecundity, then the lynx population just isn't going to have as much resource to eat. So it's a very cool story. I'm going to show you just a really cool little clip, about 30 seconds of a nature show on the remarkable rabbit. There's some kind of creepy things about rabbits, but I know some of you have some time on your hand. I'll give you a little sneak preview, and then you might take the opportunity to go and watch the whole show.
These adorable, seemingly passive furballs are in fact the ultimate survivors. Within their bite-sized frame lies a fighter, able to outwit the many predators that surround them. From frozen forests to concrete jungles, we take you to world. We'll reveal how remarkable rabbits really are.
I mostly just showed you because the baby rabbits were so darn cute. So there's a few other things going on here. So we kind of related that idea of biotic potential and carrying capacity to our selected and case-selected species. We looked at how populations can be cyclic in a predator-prey relationship. The last essential knowledge part that we want to take a look at here in this section is what happens when a population exceeds its carrying capacity. And there's 2 big ideas that we want to see here. One is that population can dramatically overshoot, and this happens because there's a little bit of a lag time between that population reproducing and when they actually use up all the resources and their population drops back. So this is another sort of classic ecological data set where we look at the reindeer population on St. Matthew Island. They were introduced into an island ecosystem, so they had a pretty finite area, isolated area with a finite amount of resources. And you can see that the population took off. They just loved St. Matthew's Island. They eat lichens, and there were a lot of lichens there. And so they skyrocketed in a relatively short period of time to a population of more than 6,000. 2 years later, 99% of that herd had starved to death, and they had a dramatic dieback or crash to their population. And again, because of those density-dependent factors that we looked at, disease, competition, and that competition couldn't even be infighting for mates within the species. But they greatly overgrazed and ate all of their food supply, and there was nothing left. They ran up against those density-dependent factors. So let's do a quick check for understanding. We covered quite a bit of information here. 2 days ago, when we talked about island biogeography, I said I'm going to kind of skip over and come back to that idea of generalist specialists. So we can look at this question now and relate island biogeography to what we just talked about. Highly specialized species tend to evolve on islands because of the environmental conditions and resource availability. Based on the theory of island biogeography, which of the following would most likely experience the greatest decline of specialist species if an invasive species immigrated from the mainland? Take a second to look at that one. Excuse me. You should have said a very small island in close proximity to the mainland, because that would be the easiest one for large numbers of invasive species to immigrate to. Next, we have a survivorship curve. This is such a fun question. A certain species of dinosaur laid large number of eggs, and the hatchlings had, I'm going to move my little thing here. The hatchlings had high mortality early in life, but if they survived, the young dinosaurs were able to grow at a rapid pace, disperse into the environment in order to thrive. Based on this information and the graph above, which of the following best characterizes the species of the dinosaur? Not all dinosaurs were that. So there's 2 parts to this question, and you have to get them both right. A, is it an R or K strategist? And B, is it a type 1 or a type 3 survival? And hopefully you got that dinosaurs were R strategists because of the fact that they laid a lot of young and had a very rapid rate of dispersion, and many of them did not survive into adulthood. They were early lost species. Another great question to interpret which of these models correctly shows or displays the population size over time of an R-selected species that has just colonized a new habitat with abundant resources. And you should see that one that's showing that, pick that letter A, that's showing that exponential growth. There's abundant resources, so I'm guessing this is probably kind of representing the carrying capacity. They just shot right over that carrying capacity because they're R-selected, they just moved in there, they reproduced very rapidly, and there was no resistance factors early on limiting their population. So let's kind of go through a debrief of how we're going to sort of apply this idea to a larger environmental issue. And that's the idea of ecological management and restoration of wildlife habitat. Dr. Sowell and I a couple of times have taken you to the African savanna, and we're going to go there again today for just a couple of minutes, looking at a population of wildebeest. So I'm going to play just a couple of minutes of the video clip showing us during this restoration process what happens to the wildebeest population, and then we'll take a look at your homework for tonight.
We found in the mid-1970s that the buffalo population was finally stabilizing at around 75,000 pounds. Meanwhile, the wildebeest population was continuing to decline and climbed at a very fast rate.
Between 1961 and 1973, the wildebeest populations had tripled, reaching 770,000 individuals. Park officials began to worry they were growing out of control.
Some people thought that we needed to do something about it, needed to reduce the population because it may have caused damage to the environment. There was a lot of opinion. We decided that we let biology follow its natural course and see what happens.
The population continued to grow until 1977, when it peaked at 1.4 million, the largest herd of large herbivores in the world. The big question was, why had they stopped increasing?
And I'm going to stop it there, and I'm going to let you think about that a little bit. Remember what Dr. Sowell talked about, I think it was yesterday, with trophic the cascades and bottom-up or top-down forces that control a population. So think about that for a little bit. Would that have been a top-down forcing that controlled the wildebeest population? That's pretty crazy growth. Why is it that they all of a sudden leveled out? Did it have something to do with their predators, or was it a bottom-up forcing, something to do with their food source? So I'll let you think about that, and you can we'll come back to that again tomorrow. So let's take a look at the our objectives or goals for today. Describe characteristics of R and K selected species. Relate reproductive strategies to whether they are generalist or specialist. Kind of tie that all in together. Interpret a survivorship curve and explain the survival rate of different species. Again, relating it to R and K selected. Describe factors that limit growth, all those density dependent and independent factors, and explain how resource availability affects population growth. The idea of overshoot and dieback, and animals increase mortality, or animals like the snowshoe hare changing their fecundity. And then our big skill that we looked at was analyzing a model or visual representation of data to explain an environmental concept. So I'm going to introduce your practice question, your homework for tonight. Remember, we have all of these task verbs. You're going to see a couple of different ones today, but no actual calculations. And there's a couple different parts to the question. I'm going to kind of walk you through a little bit of graph interpretation to get you started. So as I look at this, I want to begin. Let me back up just a second here. The first comment that Dr. Saul and I, the first idea that we want you to carry forward when you get to the national exam and your 2 FRQ is read the entire question from start to finish before you start answering. When you look at the rubrics that we're providing you and what qualifies as an adequate answer, that answer is going to come to you rather quickly. What we find both in our classes with our students as well as at the reading, when we're reading students from all over the country that have responded to these FRQs, it's pretty obvious that students just read one little prompt at a time and aren't really processing what that question's saying. They kind of puke out the first thing that comes into their head. And the reason we know that this is the strategy a lot of kids use is because you can almost see as they're halfway through writing, they're kind of like, oh, sugar. I just realized as I started writing about this that I wasn't really thinking about it the right way, or I came up with a better example or a better way to explain it. So if you take that first couple of minutes to read the entire question, where's it starting, where's it going, and start jotting notes about what you see there. Process that question as you're reading it. The answer that you write is going to come much more easily. I know it's hard. Just sit back and take a deep breath. So as I start reading this question, describe. So focus in. I've got that describe word. I would underline that. 2, I can only use my first 2, so I want to think about it. Don't waste time writing answers that aren't good. Take the time to think and process it. Put your best 2 answers forward. 2 characteristics of invasive species that allow them to outcompete native species. Well, I'm going to go back up to my graph here for a minute because letter B is asking me to summarize some things about the graph. And even before I look at what it's asking me about the graph, it's hard for me sometimes to both process what's on the graph and be interpreting the question that they're asking me about the graph at the same time. So if you see a graph, you know they're going to ask you things about the relationships on that graph. So go ahead and make sense of it on its own first, and then read what they want you to know about that. So I have time. I know it didn't show up in here. There it is. We've got this little background information. So the United States Forest Service ecologists periodically sample plant biodiversity in Mauna Kea, Hawaii between the years 2000 and 2012, 2000 to 2012. Notice there's a key piece of information they give me here, that this was a 12-year period of drought. So during a 12-year period of drought, they were looking at the relative abundance of 2 different types of grasses. One of them is an invasive grass and one of them is a native grass, and then they've given me the total abundance of grass, both of them together. So even before I read what they want me to say about the graph, I'm going to make sense of it. Over a period of 12 years of drought, there was a change in the number of plants per unit area. This is the number of plants per 100 square meters, and I can see that in general, the number of invasive species went up and the number of native species went down over that 12-year period of drought. Now when I read these questions, I'm not stressing out about, oh shoot, they're asking me something and now I have to go interpret this graph. It took me 2 minutes to go ahead and do all that graph interpretation. Now when I read these questions, they're going to be pretty straightforward to me. So you've got an A, a B, looking at the graph itself. Letter C is talking a little bit about integrated pest management, and then we got a little bit of experimental design here. Our goal is that you just nail that experimental design question because you're getting to practice it in every one of our review lessons. So complete this for homework. You're going to grade it at the beginning of class tomorrow. Thank you so much for joining us in our virtual classroom. Dr. Saul and I are really enjoying working with you and helping you prepare for the national exam in this time of difficulty. We know things are hard right now, but try to be a light for somebody. Try to think of somebody that probably has it worse than you do in some way. Think of something that you can do to maybe make their life a little better. So Dr. Sewell will be here tomorrow talking about human population, and you'll take a look at your FRQ. Have a great rest of your day, guys. See you tomorrow for the next day.
Hello, AP Environmental Science students. Welcome back. So my name is Dr. Sowell, and I teach APES down here in Jacksonville, Florida, at Darnell Cookman Middle High School. So I just want to do one more time the updates for this year's exam. So you can see when our exam is, May 18th, and there are the times below. And again, only 2 FRQs this year because of our coronavirus situation. Only 2 FRQs taking it home, with question 1 being based on an investigation of some sort, either you investigating or you proposing an investigation or parts of an investigation, or perhaps analyzing someone else's investigation. And then the second one is proposing a solution to an environmental problem. So a little bit more details down here below about what skills you will need to do those. First of all, Ms. Fassler and I just wanted to express how proud of everybody we are. This is a unique situation, and reviewing for an AP exam, at least I know in my classroom, did not look like this for the last couple of years. It's, us all in a room together, hammering stuff out, talking. So this is new. This is different. So the fact that you are back again, slugging through these reviews, bravo, bravo, bravo. Good for you. I just want to give a shout out to Neil from Chico, California. Neil, if you're out there, keep up the good work. He and I've been emailing back and forth. He's doing this as an independent study. So bravo for those of you who are doing this on your own, which is even more of a challenge. But everybody keep up the good work. So let's start with the homework from Ms. Fassler. This question starts us off with the U.S. Forest Service ecologists periodically sample plant diversity on Mauna Kea, Hawaii between 2000 and 2012 during a 12-year period of drought, keyword there, to determine the relative abundances of native hardstem lovegrass versus non-native fountain grass. I'll reiterate what Ms. Fassler said here yesterday. Slow down and read the entire question before you start to answer. Now you may have your own strategies, but that's the strategy I tell my students. Slow down and read every word so that you know what the entirety of the question is asking, as opposed to what AI might be asking, for example. And so there's the opening here, and then it gives you a graph, so we can kind of look at the graph in terms of the axes. What are the 3 data sets that are displayed on the graph? The title, the abundance of 2 different grasses between 2000 and 2012. I know when I first read this FRQ, I kept stumbling on native hardstem lovegrass, non-native fountain grass. I mean, both grasses, they both have complex names, so that was a place that I know I had to slow down a little bit. So let's start looking at some answers. So A said, describe 2 characteristics of invasive plants that help them outcompete native plants. So your description, not an identification, needed to include how that helps them outcompete native plants. So this is worth 2 points, 1 for each. You could have said something about the range of tolerance. Perhaps they have, there is some abiotic factor of their environment that the invasive species are more tolerant of in terms of extremes than the native species that would give them an advantage. They might be a generalist, so that gives them a little bit advantage over native species that maybe are more specialist. And then the category being our selected species, or our species, our strategists, is a huge characteristic because they typically propagate or reproduce earlier in their life cycle, and when they do, they reproduce a lot. Think of like a fern, for example, millions and millions and millions of spores coming out. And so you can also talk about invasive species lacking natural predators or diseases that control their populations. So any of those two descriptions would have got you points here for A. B really has you looking at the graph. So it says based on the data in the graph, tells you right there, look at the graph. Identify the year in which the abundance of native plants versus invasive plants is nearly equal. So you could go over here and here's our invasive and native, and where are they most equal? Right around there. So you pick a year and it could have been 2001 or 2002. So a little piece of FRQ advice. If you are asked to identify a value from a graph, pick a value. What would not get you points typically, I can't say this is a rule everywhere, but typically you would not want to say the year in which the abundance of native plants is nearly equal to the invasive is somewhere around 2002 or somewhere between 2000 and 2004. That's not identifying a value. So it says identify the year, not a range of years. Little advice. And the next one says describe the change. So in overall abundance. So overall abundance is this one right here. So it's going from around 340 down to about 300. Again, this word is important. It says describe, not identify. Identify might be, it goes down, but describe, you need a little bit more of a description there. So you could say something like the plant abundance decreases from approximately 300 plants per square 100 meters down to 300, or you might say it decreases approximately 10%. So again, you're providing some description of the change, not just saying, it went down. I explain what the trend in relative abundance of native hardstem lovegrass and invasive fountain grass over the 12-year period implies about each species' ability to withstand drought conditions. First thing you should key in on is the word explain. And remember those task verbs mean something. So explain how or explain why something. I've given you a reminder here. So it says provide information about how or why a relationship, process, pattern, position, situation, or outcome occurs using evidence and or reasoning to support or qualify a claim. So there's a description part of this, but there's also a justification. There should be some verbs in there that you know what you're talking about. So here's an example. Over the 12-year period of drought, the relative abundance of native hardstem lovegrass decreased, while the abundance of invasive fountain grass increased. Period. This would imply that the invasive fountain grass is more drought tolerant than the native hardstem lovegrass. That's an explanation. C, explain, there's word again, how loss of species diversity would affect the stability of an ecosystem. And I know I've mentioned this before in Unit 1, Fassler mentioned it the other day, that there's a relationship between species richness and biodiversity and the stability of an ecosystem. How resistant is the ecosystem to change, and then how resilient, how much can bounce back from that change. And so again, think about the relationship between the stability of a tundra versus the stability of a tropical rainforest, for example. So in this case, we're looking for how explaining a loss of diversity would affect the stability. So you could say something like the greater the species diversity, the better it can withstand stressors. And so you can also say ecosystems that have a larger number of species have a greater chance to recover more quickly from a disruption. So the conversation we had the other day about disruptions and disturbances, how ecosystems respond to that is related to species biodiversity. And then finally, if you look just at plant species themselves, the greater the biodiversity there, the greater the productivity for that whole ecosystem. Remember we talked the other day about NPP, net primary productivity, being the battery that drives the rest of the trophic levels above it and supports the whole food web. So that would give you a more stable trophic structure as well. And D, last part, based on the data in the graph, the Forest Service decided that a coordinated attempt should be made to remove the non-native fountain grass to protect the native grasses, following an integrated pest management approach, IPM. Okay, so they're going to do an IPM approach to reduce this invasive species. So first, DI says describe IPM. Well, remember, describe is provide the relevant characteristics of the topic. So what are the relevant characteristics of the topic? When I think of IPM, I think of in contrast to just a blanket use of broad spectrum pesticide. I kind of think about its opposite. So instead of a blanket use of broad spectrum pesticide being your only strategy to reduce pests, IPM I think of a more holistic approach that involves using biological control, chemical control, physical controls, reducing a pest population down to a manageable level that's economically tolerable. So that's what I think of. So let's see what the answer here says. Integrated pest management is a combination of methods used to effectively control pest species while minimizing the disruption to the environment. I think that's a nice point there. Especially limiting the introduction of chemicals into the environment. These methods include physical, biological, and limited chemical. Remember, characteristic of IPM is not that we do not use pesticides. It just means that we use it in a measured way, in a limited manner. And finally, we got into the experiment part. So it says the ecologists want to begin their IPM program with a physical control in a managed area and establish a 10-hectare plot in which they will test their efforts. Based on the data in the graph and the information provided, identify a testable question. So they could ask, how will the physical control or removal of invasive fountain grass affect the relative abundance of native hardstem lovegrass? Maybe down here, how will the local environment respond to the physical control or removal of fountain grass? So when you're trying to identify a testable question, remember it's ideally both the independent and dependent variables are reflected in the question, and then the way those variables are described, you can clearly see how they could be quantified or what kind of data collection you might make for both of those. And then the last part, describe a research method that they could use. So again, this is part of the scientific experiment skill that we looked at before. So you could say as part of that experiment, they could physically remove the fountain grass on an identified schedule and then do nothing to the lovegrass. Or if we jump down to the bottom, you might physically remove both types of grasses from the test plot at the beginning of the trial and then reseed the area with hardstem lovegrass. So the question is asking you for a description of a reasonable keyword there, research method that they could use in the control effort. So many possibilities for that. All right, so hopefully you did well on that FRQ. I'll leave you with an FRQ for homework tonight as well that Ms. Fassler will go over tomorrow. So what are we talking about today? We're talking about us people. So Ms. Fassler did a brilliant job yesterday of talking about the population dynamics of animals and plants, talking about R species and K species, talking about carrying capacity, things that limit the biotic potential of a population. Well, we obviously are animals as well. We're a species on this planet, but we don't typically follow sometimes the pattern that a warren of rabbits might follow in a field. So we're going to look at some differences today, some things that make human populations unique and different. So our goal, we're going to look at age structure diagrams, we're going to look at total fertility rate, basic human population dynamics, and then the demographic transition. And then through doing that, we'll also look at visual representations and data analysis. I think that for this particular lesson, it's useful to kind of go back into the bigger picture. So remember, our overall enduring understanding is human populations change in reaction to a variety of factors, including social and cultural. Now, Ms. Fassler was talking about populations of a fish species or a rabbit species or a lynx species. This didn't include social and cultural factors. Here we do a little bit more. I think this is a perfect place to really emphasize visual representations and models, from the ability to just describe the pieces and parts going on in that model, and then going all the way down to say, okay, I understand this model. How can I use it in a new context? I mean, clearly we have two essential visual representations or models here in this unit. Is we look at the age structure diagram and the demographic transition model. All right, so what do we really need to know? So let's start with Unit 3, Topic 6, and this is our age structure diagrams. So after we chat for a few minutes, you should be able to explain age structure diagrams as a good goal. So how are we going to get there? We're first going to describe just what's going on inside of an age structure diagram. Not really use it, just who are the pieces and parts, who are the players, what's being told there. And then we're going to use that model to explain population growth. I do want to point out that sometimes you will see age structure diagrams described as population pyramids. Those words are not 100% interchangeable, but a lot of times you will see one versus the other. We in our curriculum typically follow age structure diagrams. That's the wording we use. All right, so here's one. This is the age structure diagram of Uganda from 2020. I just pulled these a couple of days ago. Here's another one. This is us, United States this year. And here's Japan. The first thing you should recognize is they all look different. So if they look different, that means they're telling different stories. And I should be able to look at an age structure diagram and come to a more robust understanding of what's going on in the population dynamics of that particular country. Age structure diagrams typically are done on a country level. So let's just break down the pieces and parts here. So this is the United States one for this year. So the first thing you'll notice is we've got a male and a female side. The left side here is male, the right side here is female. On the bottom you can see population, and on the y-axis you can see age. So just as an example, in 2020 there were approximately 10 million females between the ages of 0 and 4. 4. That's how you could read a piece of that data. That age group is particularly useful from 0 to 14 because we call that the pre-reproductive cohort or group. So the pre-reproductive group is 0 to 14. Then we have this bigger chunk that is reproductive, 15 to 44, and then post-reproductive after 45. Now, obviously, a female can have children before or after these strict demarcations here, but this is an average. This is just a cohort definition to use. So those come into play in a little bit. All right, so let's look at these 3 age structure diagrams and look at that particular grouping. So if we look at Uganda, the vast majority of this age structure diagram is composed of this young pre-reproductive group. As opposed to the United States, it's almost in line with some of the other cohorts above it. Whereas Japan, this pre-reproductive group is much smaller than what we have above. So these 3 countries give us an example of what we can do by looking at that pre-reproductive stage. What we're looking at here is population momentum. So this is a prediction of future growth. The higher the percentage of people in that pre-reproductive cohort, the more the population will grow as these individuals mature into the reproductive cohort. Meaning, if the country of Uganda has a very, very large pre-reproductive group, that means in the near future they will become part of the reproductive cohort and population will continue to grow. The United States, growth will probably be a little less, pretty stable. And then in Japan, we can see the number of individuals at the pre-reproductive level are quite smaller, so that may indicate a slower or even a negative population momentum in the near future. This inverted pyramid shape of Japan is particularly useful to understand the fact that this might put social pressures on the economy and the social system of Japan because the vast majority of the population are older. And typically, in most societies, the older generations, because they're no longer working, rely on the economic and social support of the younger generation. Well, in this case, we've got a much stronger population of older individuals than younger individuals. So just the shape of the pyramid alone can tell us something about what might be going on in the society. The rule of thumb is this: a rapidly growing population will, as a rule, have a higher proportion of younger people compared to stable or declining population. In other words, when you look at an age structure diagram, if it has a very large base, future growth will be higher than if it had something like Japan's, which is a negative growth. Okay? So we've been talking about growth rate. We represent that by R. We saw that with Ms. Fassler yesterday when she was talking about the population growth graphs that she was looking at. Now, this is typically expressed as a percent. R is a percentage. Now, we know in the AP exam this particular year, you will not be asked to perform calculation. So I am going to show you how to calculate R, but not because I assume that you're going to have to, because you won't. But you may be presented with data like R values and have to make an interpretation based on that. So while you may not have to calculate R, you need to understand how R is derived and what it means. So basically, the growth rate is birth minus death over 10. That's the basic formula. Now, there are also issues of immigration and emigration, but we're not going to deal with those at this point. So let's just take Japan, for example. Japan this year has a crude birth rate of 7 births per 1,000 individuals. We can just really relate that as a birth equals 7. The reason we can just reduce that to 7 is we're making a percentage here. So because this is already over 1,000, we reduce it to 7 and then divide by 10. That's probably a bad explanation, but all you really need to know is the growth rate is birth minus death over 10. So in this situation, for Japan, 7 minus 10 divided by 10, so we're looking at a negative 0.3% growth rate. So that means that this population is not growing, it's shrinking by a rate of negative 0.3%. That's R. So here's the R's for those 3 countries we're looking at. So Uganda is 3.3, very high growth rate. Japan is negative 0.3, slowing down, going negative. And you'll see United States is 0.7. So it's pretty stable. It's not as big as something like Uganda would be. So again, shape of the pyramid, you should be able to kind of relate that to its R, its growth rate. You can also look at one country over time. So here we were looking at 3 different countries for this year. You can also look at one country over time. So this is Brazil in 1950. And just on this snapshot of a moment, you should be able to start telling a story, maybe perhaps of the percentage of pre-reproductive individuals, what might that indicate for the population momentum and future growth rate. And then if we start looking at over time, that's 1950, 1960, 1970, 1980, 1990, 2000, 2010, and this year. So it's really interesting. If you just look at 1960 to 1970, really don't notice some difference. There's some reduction in some of the numbers. But when you really compare these 2 years at the end, or the beginning and the end, 1950 and 2020, huge difference. Their population structure looks different. Their age structure diagram looks different. There's something different going on in the society of Brazil in 2020 that wasn't going on in 1950. And so we could look at things like industrialization or development, urbanization, education, income levels, but also cultural influences. So I'm going to let you listen to an NPR story. It's a couple minutes long that really dives into some of the, quite unique and fascinating things that would take a country from an age structure diagram that looks like this to something like this today.
In Brazil, there's been a demographic shift that has astonished social scientists. In 50 years, the fertility rate tumbled to fewer than 2 children per woman on average, lower than in the United States. Demographers say it's because the country is richer and more urban, but they also point to Brazil's hugely popular soap operas and the portrayal of small, glamorous families. NPR's Juan Ferrero has the story from Rio de Janeiro.
Veronica Marquez has a husband, a nice apartment in a trendy district, and a career she loves. Talking in a restaurant near her office in Rio, Marquez explains that she's 31 and doesn't have children.
I'm planning to have kids when I have a bigger career, when I raise more money, and maybe when I have my life in another step.
And when she does have kids, she says, it'll be 2 tops. Smart, educated, ambitious, Marquez is typical of a growing number of Brazilian women who are focused more on their careers. If she does have 2 children, it'll be right in line with the average these days for a Brazilian woman. Barely 2 generations ago, it was 6 children per woman. Then the fertility rate in Latin America began to plunge, though it was most pronounced here in Brazil. The latest figures, in fact, show that the fertility rate stands at just under 1.9 children per woman, says Susana Cadenaghi, a demographer in Brazil Census Bureau.
There are a lot of reasons for that drop in Brazil, and most of them has to do with the modernization, this new way of thinking. Women are modern, and they take care of their own lives.
Brazil's fast urbanization means millions of rural poor migrated to cities where big families are a financial drain. And in a country where abortion is illegal and the Catholic Church frowns on birth control, women have embraced family planning any way they could, says Cadenaghi.
They have more to say about their reproductive life than the men. Men interfere less in their lives than would in other countries.
And there's another factor, one documented in studies by the Inter-American Development Bank and the University of Texas, the role of the telenovela, or soap opera. In Finnish, now by the most popular Brazil's telenovelas these days, the characters are often rich and cosmopolitan and have few children, if any at all.
Ah, meu Deus, Solange, você tá indo rápido demais, amiga. Homem não gosta de mulher tão iniciativa desse jeito.
It's been a recurring theme in soaps for decades, says Maria Lopez of the Center for the Study of the Telenovela.
Eu creo que no hay duda de que la telenovela.
She says there's no doubt that the appealing lives presented in the soaps play a role in the falling fertility rate. Other factors also are at play, including the expanding role in the workforce for Brazilian women, whose educational level has also soared. Still, it's not just the educated and affluent who've seen the fertility rate plunge. Demographers say they see it among the poor too, and in rural as well as urban areas. At a new restaurant in a working-class district on Rio's outskirts, the 5 women owners all come from big families. Priscilla da Silva chops tomatoes in preparation for the lunchtime crowd. She says times have changed.
Antigamente, queria ter 4.
Before, I wanted 4 children, she says, and had even picked out names. But now, I just want 1, she says.
Situação. Hoje em dia, você criar filho é muito difícil.
It's too hard these days, Silva adds. You have to pay for schooling, for healthcare. There are all kinds of costs. And besides, she says, she's got a growing business to run. Juan Ferrero, NPR News.
So I just think that's really cool. It's great to hear the actual voices of the individuals experiencing these changes as opposed to just hearing me blah 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 about it. So one of the things I mentioned in there was total fertility rate. So this is Unit 3, Topic 7. And so basically the total fertility rate is the number of children the average woman has in her lifetime. This is on average per country. So what might affect that? Well, you heard a lot of those things in the story, but the age at which females first have a child, what is culturally and socially the norm for that particular country. Educational opportunities, huge impact on total fertility rate. To what degree females are educated in the country. Access to family planning, government acts and policies. You may have heard about the one-child policy in China, for example. Other countries have other policies or acts or laws that might have been placed in terms of population control. So if we look at TFR, total fertility rate, over the course of the last 60 or 70 years or so. So in 1960, the global total fertility rate average was around 5. That means the average female on the planet, female human being, had 5 children on average. Now, a little less than half of that, 2.4. So we've seen a dramatic decrease in the number of children. Why? There are many factors. So here are the two from the ones we looked at before. Right now, the total fertility rate in the United States is around 1.8, meaning the average woman in the United States is having 1.8 children, as opposed to Uganda, which is 3.3. Now, that's useful in terms of comparing it to this concept called replacement level fertility. If we have 2 people and they have 2 children, they've replaced themselves. So that means that when the 2 parents die, they're replaced by their 2 children. So replacement level means you're simply replacing the parents. And ideally it would be 2 because, 2 would match. But because there's so much infant mortality in certain countries, it's actually a little higher than 2. So if we compare this replacement level fertility with total fertility rate of a country, we might be able to see a relationship there. And so if the fertility rate is at replacement levels, a population is relatively stable. So that's kind of where the United States are. We're a little bit lower than replacement level, but we're not seeing the massive population growth that Uganda is because their total fertility rate is much higher than the replacement level fertility. So I mentioned before that one of the reasons that replacement level fertility is higher than 2 is because of infant mortality rates, the number of children below the age of 1 to die per 1,000 births. And in some countries it's much higher than others. And for the reasons you could probably guess, so access to clean water and nutrition or sanitation, prenatal care is huge. And again, education of females. So if we look at infant mortality rate globally, in 1990 we were looking at a very high value, close to 65, and now we're looking at something around 29. So the global infant mortality rate has decreased as well. But it's really interesting to think about what's going on within a country. So far we've been talking about Uganda as if it's all the same, or the United States as if it's all the same. Well, we know we're not. And so the infant mortality rate actually is different in different parts of our country as well for socioeconomic reasons and other reasons as well. So here are the 3 countries that we've been looking at. So the infant mortality rate is 33 in Uganda. That means out of every 1,000 live births, 33 do not make it past their first birthday. Whereas the United States, it's an average of 5. In Japan, it is 2. So we're starting to kind of throw these numbers onto these 3 countries in terms of replacement level, fertility, growth rates, total fertility rates, infant mortality rates. You should have a range of what's acceptable or normal. So you wouldn't have an infant mortality rate of 3,000, for example. So you've got to kind of think of what's normal for these values and then start putting them together to tell a story of what's going on in a country. So now we're going to move into kind of the world as a whole. So by the end of this particular section, 3.8, you should be able to explain how human populations experience growth and decline. So to get there, we'll look at the idea of the carrying capacity for humans on the planet. We'll describe factors that affect our overall population change. And then we're going to talk about this little discrete rule called the rule of 70. So here is a screenshot of the U.S. Census, the world census. I just grabbed it a couple hours ago. So you can see currently the U.S. population is 329.5 million people, whereas the world population is at 7.6 billion people. And here you can see the top 10 most populous countries. I think it's interesting to look at China and India, how close they are. Most demographers agree that India will take over the first place from China soon. The United States, Indonesia, Pakistan, Nigeria, Brazil, Bangladesh, Russia, and Mexico rounding out the top 10. It is interesting to note here, on average, there's 1 birth every 8 seconds on the planet and 1 death every 11 seconds. Right there tells you that we're, this is clearly an average. This is not something that is country specific. This is an average everywhere. So just have a general idea of what the population of the planet and the United States is. So let's look at the world population. The overall growth curve here is exponential. It's growing at a higher and higher rate, especially since the Industrial Revolution. And if you remember the conversation yesterday from Ms. Sassler, we don't see us experiencing the effects of a carrying capacity here. We're not seemingly being limited by the environment, the environmental resistance or stressors in the environment. Contrast that to the conversation that you had yesterday about carrying capacity in other organisms, where the biotic potential is counteracted by the environmental resistance to create the carrying capacity, the relatively stable population size. This population is limited by the environment, factors in the environment. So the question that should immediately come to your head is, well, where's our carrying capacity? So at some point, are we going to experience the same thing that the other organisms do? Some people argue that we've already passed our carrying capacity. Some people argue we haven't reached it yet. And it's useful to start that with someone named Thomas Malthus. So this is the late 1700s. He described population this way. He said, hey, the human population is growing exponentially. So here's this curve right here, the exponential population growth of humans. But he said, unfortunately, food production is pretty linear. We don't see that exponential growth in food production. So at some point, we're going to reach this catastrophe point, the point in which we just don't have enough food, and so population is going to start to decline. Some people disagree with that and say that because of the creativity and agricultural innovation that we've accomplished, we simply increase the carrying capacity. So just think about all the things that are involved in the Green Revolution or all the current modern agricultural practices that greatly increase yield. Well, maybe that's enough to raise the carrying capacity for human beings on the planet. So overall, what influences that other than food production? Well, birth and death rates clearly, infant mortality rates, access to family planning, good nutrition, education of females, and postponement of marriage. You should start seeing some patterns here at the country level and at the global level. Now, we could stop and go into lots of case studies here. We could look at, education of females in Nigeria, for example, or we could look at the one-child policy in China or some of the educational programs in Brazil, but they all have these common themes going on. So instead of going into those case studies, I thought we would just take a broader look here and look at themes. So it's also affected by density-independent factors like a hurricane or a fire or a drought, as opposed to density-dependent factors such as food and water, other resources, disease, or territory size. So Ms. Fassler started this conversation the other day, reminding you that a hurricane is going to have the same destructive power to a population, whether the population is small or large. The density of the population does not impact the power of a hurricane, as opposed to something like disease, in which we know the proximity and density of organism can speed up the transmission of that disease. So density-independent, density-dependent. And finally, we get to this rule of 70. And again, you will not be asked to do calculations on the exam, but you may be asked to interpret what a doubling time means. So basically, the rule of 70 says, what's the average, or what's the estimated number of years it'll take for a country's population to double? So the formula is pretty simple. The doubling time is 70 divided by R expressed as a percentage. So for example, right now, with our growth rate of 0.7, it will take 100 years for the United States to double its population, as opposed to Uganda right now, if everything stays the same, they will double in 21.2 years. So you should be able to think about the relationship between doubling time and economic development of a country and its place on the demographic transition that we'll look at in a few minutes, or right now. So this demographic transition, this is a great model. It's a great place for us to practice our visual understanding of a model and looking at a graph. So to get to this understanding of the demographic transition model, we'll first just describe it, what's going on inside that model. And then we'll look at some comparisons between those age structure diagrams we did at the beginning and this demographic transition here. And then finally, we'll end today with looking at some basic characteristics of developing and developed countries and where they may fit along this model. So let's just pick apart the model at this point. So first thing you'll notice at the bottom is time. So this is years at the bottom, time is at the bottom, x-axis. And on the y-axis, or at the very top, we've got these labels: stage 1, stage 2, stage 3, stage 4. Let me stop here and say that APES, AP Environmental Science, uses a 4-stage model of the demographic transition. Some places you will see a 5-stage model. What's going on inside the model doesn't change. It's just a change in where they've made these delineations into separate stages. Okay? But we use pre-industrial, transitional, industrial, post-industrial. On the left-hand side, we have birth and death rates. We've talked about that before. And on the right, we have the population size. So let's kind of go through from left and right and see what story this model is telling. So at the beginning, beginning, when a country first begins its travel through the demographic transition, its birth and death rates are going to be relatively high and relatively equal. So if there's an equal number about of birth and deaths going on, the population is going to be pretty stable. It's very rare to find societies like this on the planet still today. This is characterized by lots of warfare and instability, struggling for resources, clearly no healthcare, medicine, education, things like that. But as a country moves out of that, we get into this transitional stage where something really unique happens, and this is definitely a place for you to think about birth and death rates. So the first thing that starts to happen is we see this drop in death rate. So infant mortality rate starts to go down. We start seeing improvements in healthcare and medicine, so the death rate goes down. However, the birth rate kind of stays where it was for a while. And if we have many more births than we do deaths, the population is going to increase. So this kind of gap between these lines here pushes the overall population forward. And then we start to see the birth rates coming down to meet the death rate. So death rate drops first, birth rates drop, and if birth and death are getting closer together, like they were over here, we should start seeing a decrease in the population, or a stabilization of the population, and eventually a decrease. The population should decrease if the number of deaths are now more than the number of births. So we can imagine a country over a long period of time going through every single one of these stages. And currently today, we have some countries here in the very end of the post-industrial stage, and we still have some countries at the transitional industrial stage as well. So here's an example of one of those that was 5 delineations, but the story of what's going on is still the same. I want to point out the reasons for changes in birth and the reasons and changes for death. So one of the key reasons why birth rates are still high up here is because this is typically going to be a more agricultural society, and many children needed for farming. We still have a rather significant infant mortality rate, but social and cultural reasons, as well as a lack of family planning, all feed into the birth rate still staying pretty high, whereas the death rate has dropped. There's less disease and famine, there's better healthcare, better water supply, and then eventually we get to a place where those things even out at the same level, and we start to see population decrease. And we see that with family planning, good healthcare, improving status of women, including education, and later marriages. And we start to hear that in the conversation of some of those Brazilian women in the NPR stories. So now let's see if we can tack on some of those population pyramids to this model. They don't coincide 100% perfectly, but you should be able to look at population pyramid and figure out where it might land on the demographic transition. So for example, as we move from pre-industrial to transitional and into industrial, we still have this large base, this high population growth, lots of individuals in the pre-reproductive cohort. But then as we start to go through the industrial stage, we start to even out, so we get a little bit more stable population. And then finally something like this, where we would start to see a decrease in the base of the pyramid. So for any one of these, like this one for example, noting its place on the demographic transition and its shape, could you tell stories about this country? Could you maybe speculate on infant mortality rate or economic development or status and education of females? Those are the things that you would be asked to do on exams. All right, so we finally we're going to end today with this idea of developing versus developed countries. It's not, clearly countries are very heterogeneous, and we can't categorize a whole country as developed or developing. Some textbooks will use LDC and HDC, less developed and highly developed. But if we paint with a broad brush, we want some generalizations. We can typically say levels of industrialization and income play a role here. So less industrialized and less overall income could be developing country. Total fertility rates and infant mortality rates would be higher in the developing country. Number of children in the workforce, especially in agricultural fields, is going to be higher in developing countries. Population growth are going to be stronger in developing countries because their birth rate is still high. And then as you become developed, you're going to have better nutrition, sanitation, clean water, education, healthcare, all of those things. So I want to end with playing just a minute or two of the population pyramid TED talk that I used.
Russia, with the largest territory in the world, has roughly the same total population as Nigeria, a country 1/16 its size. But this similarity won't last long. One of the populations is rapidly growing, while the other is slowly declining. What can this tell us about the two countries? Population statistics are some of the most important data social scientists and policy experts have to work with. But understanding a country's situation and making accurate predictions requires knowing not just the total size of the population, but its internal characteristics, such as age and gender distribution. So how can we keep track of all that data in a way that makes it easy to comprehend? Complex data is more easily interpreted through visualization, and one of the ways that demographers represent the internal distribution of a population is the population pyramid. Here, the data is divided by gender, with females on one side and males on the other. The population numbers are shown for each 5-year age interval, starting from 0 to 4 and continuing up to 100 and up. These intervals are grouped together into pre-reproductive, 0 to 14, reproductive, 15 to 44, and post-reproductive years, 45 and up. Such a population pyramid can be a powerful predictor of future population trends. For example, Rwanda's population pyramid shows it to be a fast-growing country. With most of the population being in the youngest age groups at the bottom of the pyramid, the number will grow rapidly in the coming years. As today's children reach their reproductive years and have children of their own, the total population is almost certain to double within the next few decades. For our second example, let's look at Canada, where most of the population is clustered around the middle of the graph. Because there are less people in the pre-reproductive age groups than there are in the reproductive ones, the population will grow more slowly as the number of people reaching their reproductive years decreases. Finally, let's look at Japan. Because the majority of its population is in its post-reproductive years, and the number of people is smaller at each younger interval, this means that at current rates of reproduction, the population will begin to decline as fewer and fewer people reach reproductive age.
So I will highly recommend you taking a look at the second half of this. It's really interesting. They go into a little bit more detail about different countries. It's easy to find if you just Google demographic transition or population pyramids TED Talk. You'll find it really interesting. So let's do some rather quick, looking at time here, examples. So during which stage of the demographic transition shown above does population begin to experience an explosive increase in growth? So where does it begin? So you've got stage 1, stage 2, stage 3, and stage 4. Well, the answer here would be stage 2. This is when you would start to see that big uptick in population size. Here's an example of a test question we were asked to look at an age structure diagram. A country with an age distribution like that shown in the figure above is most likely a country that is experiencing rapid growth, slow or no growth, high death rate, 40% of the population under 15, or is a less developed country. Well, because it's really almost straight up and down, that points to slow or no population growth. All right, I'm going to skip that question. Feel free to go back and look at it. And then I'm going to point out our homework for tonight. So for today, we went over age structure diagrams, TFR, human population dynamics, and the demographic transition, all kind of helping you understand that human populations change in reaction to a variety of factors, including social and cultural. So for homework tonight, again, remember your task verbs, look at them. They mean something. I'm going to have you do this at RQ. And the first thing you should see is it starts with some age structure diagrams, and then there's an A, B, C, and D. Just as a reminder, anytime you see a diagram, stop and try to digest it. There's a strategy I like to use with my students called I-squared, in which you first identify and then interpret. You first go, well, what do I see? And you just simply identify things in the graph that you see. You don't try to interpret them yet. And then you go back and add up what does it mean statement to each one of those things that you saw. And that helps you to build a robust understanding of the story the graph or the image or the model is trying to tell you. It would be like trying to understand all the characters in a movie and the plot at the same time all at once. Well, no, you build up the characters and eventually you tell the story. Just like this, you need to build up what all the pieces and parts of this are to tell the story. If you're interested, that strategy is called I-squared. And if you use the link below or you just Google BSCS I-squared strategy, you should be able to find it. It's not a strategy I would recommend for use on the AP exam because it does kind of take a long time. But if you practice it several times with several different graphs and visual images, it will help your ability to do that. So again, take a look at this homework and it's faster. We'll go over the questions A, B, C, and D tomorrow. Just a reminder one more time, we know that not all students have access to the internet or a device. We're working on solutions to help students get what they need to show the best work. If you need mobile tools or connectivity or know someone who does, you can reach us directly to let us know. All right, apes, nice to see you again. Bye, see you next time.
Hi, welcome back to the APES virtual classroom. I'm so glad to see you all here today. Happy Friday. We're going to start by taking a look at the homework that you did with Dr. Sowell yesterday. I'm Ms. Hassler, and I teach at APES at Marshfield High School in Marshfield, Wisconsin. So for a warm-up, we're going to take a look at the population FRQ that you did yesterday. We are, by the end of today, halfway through our review session, so we'll be due for a little bit of celebration. You started yesterday by looking at this diagram, this model of age structure diagrams, sometimes called population pyramids, and you had 3 countries, X, Y, and Z. And the first thing you had to do is to identify which country had the largest and the smallest growth rate and explain why. So this is a really good example of that common skill that occurs in both of the 2 FRQ that you're going to write. You're going to use a model to explain an environmental concept and process. So let's dig into this. Which of those countries had the largest growth rate? You could have said that you needed to say that X had the largest growth rate, but you didn't earn that point until you explained why. And notice, let's look at this third bullet for a second. I can't just say that, oh, country X has the largest growth rate because it's got the broadest base to its pyramid. I have to explain why having a broad base would indicate a rapid population growth. And notice some of the other ways that you could have expressed that. I could talk about the percent of the population being in that pre-reproductive category or cohort. The other point then was for identifying that country Y had the slowest growth rate, and the explanations were sort of the reverse of what we did with country X. Its pre-reproductive cohort is about equal in size to those others, which should be an indicator to us that growth is slowing. There's not, it's a stable population. We might have even said zero population growth. In the next part of the question, you had to use that model to then explain something else. That's kind of, remember, that big idea of where we're going with this skill. I want to be able to use that model to explain differences in infant mortality rate in this example. So 1 point for saying either that country X had the higher or country Y had the lower infant mortality rate, one or the other, and then 1 point for the explanation. And again, they're kind of opposite of one another. So based on that age structure diagram, country Y is likely an industrialized or more developed country. And I can't just stop there, because if I simply say country Y has lower infant mortality rates because they are industrialized, I just haven't put enough meat on that explanation. My question then is, well, why do industrialized countries have lower infant mortality rates? And I'm guessing most of you honed in on something to do with access to healthcare or better nutrition or better access to safe drinking water. And then on the flip side, country X would have the higher infant mortality rate. It has the age structure diagram typical of a non-industrialized or less developed country, and they tend to have higher infant mortality rates because or due to, again, the opposite of those reasons. We then had 3 points to really describe a process. I needed to describe the changes that a country goes through as it's going through that demographic transition model that you looked at yesterday. So you needed to make sure that you talked about the changes in birth rates and death rates. You couldn't just describe what was happening in each phase, really look at that question, and I have to hone in on birth rates and death rates. So initially, birth rates and death rates are both high. In the transition period, birth rates remain high, but death rates start to decline. And in the industrial, or they would have accepted post-industrial phase, both birth and death rates are low. They tend to be they tend to cancel each other out and both be low. The last 3 points of the question had to do with an incentive that a government could implement to reduce population growth rates, how the government would implement that, and one possible drawback of that solution. So most of you probably went with an incentive or disincentive, an economic incentive or disincentive that the government could offer. For example, the government could offer free access to birth control to limit the size of your family, or the disincentive would be the reverse of that, take away access to birth control for families that had larger families than what the government would have liked them to have. And again, usually that has to do with some type of economic reward or punishment. This is about the only other big strategy that that was listed on the rubric that the government could implement. And then again, you can kind of see the ways that the government would implement that: education programs, incentives for higher education for women, because we know that when women, the higher the level of education, the lower the fertility rate. So lots of different strategies there. And then the potential drawbacks. I think a lot of students probably focused on some of the cultural, social, or religious pushback to try to tell people or mandate the size of their family. Other things like infringement on human rights. Some of these policies are difficult to enforce. Notice that if there are parts of that country, because just because we say that a country is in a certain phase of a demographic transition, think about how large our country is and how we have different regions that vary in their needs. And so a rural area may say, well, we still are largely agrarian and need to have large families. So let's take a look at where we're going today. Now that we finished unit number 3, we're starting into unit 4. We're going to have 2 lessons on unit 4. And this is another example of a unit where we're really going to dig into that common theme in both of the FRQs, what we really just introduced in the warm-up, looking at visual representations, models, quantitative data, and using the interpretation of that to then describe and explain environmental processes. When you look at the learning targets in the first part of chapter 4, we're jumping around a little bit in our organization of those. These topics are really just, they don't lend themselves in and of themselves to a lot of experimental design or solutions. So I'll tell you where we're going with our lesson today. We're going to look at plate tectonics and then kind of the atmosphere and how global weather and climate patterns are created. And we're really going to show how reviewing this core knowledge is going to allow us to apply that probably in describing and analyzing larger contextual environmental ideas that we might see on the environmental exam on May 18th. So these questions, these topics in and of themselves are going to integrate really well into a full free response question, where then we start to apply some solutions and experimental design. And you'll see what I mean as we go through the lesson. So let's start off with that first, that geologic idea of Earth systems and how they interact. And we're going to kind of draw from some of those ideas that we've already established. This idea that Earth systems interact, but overall there tends to be this state of balance. And that should sound like a common theme to you when we looked at biogeochemical cycles and the rate at which things move through them. Well, Earth material has to move through a cycle in and of itself. Those same atoms of nitrogen, phosphorus, and carbon are often found in the lithosphere, solid part of our planet. So these short or these long-term geologic processes that occur over millions of years are important in helping us really put that idea of biogeochemical cycles all together. And it helps us visualize or get an idea of where we might locate mineral resources or deposits on our planet. And that idea we're going to take into a future unit on mining resources and how we locate minerals that we mine, the techniques that we use to get them out of the ground. And remember that overarching idea that these are non-renewable resources that because of the span of time it takes to form them are present on our Earth in a finite amount. Well, and we're also going to look at how these processes have sculpted our amazing planet. And that really ties into that overarching idea of ecosystem diversity. We inherently realize that having a variety of ecosystems is important to biodiversity. Now we're going to look more at the patterns for how some of those ecosystems form. So we're going to do a quick review of the 3 types of plate tectonic boundaries or interactions that can happen at tectonic plate boundaries. And the first of those is a divergent plate boundary. And I'm going to really try and keep it to the kind of core, really big ideas that we need to take away from this and show you how we could apply that to understanding or describing some larger environmental issue. So at a divergent plate boundary, plates are rifting or tearing apart and being stretched really thin, creating this rift valley. So if you picture some Play-Doh or pie crust or pizza dough, and you stretch it and stretch it and stretch it, and it gets thinner and thinner and thinner as you do that, that's what is creating this rift valley. And I'll show you some actual images, not just a cartoon image, in a second. The other big thing we want to understand about the processes at these divergent plate boundaries is that when I stretch that lithosphere really thin, upwelling of magma, because that's really thin and there's a weakness there because it's been stretched so thin, that upwelling of magma splits that earth crust and pushes those plates apart, and that's what we call seafloor spreading when that happens on oceanic crust. We also create this mid-ocean ridge. So where that seafloor spreads, where that magma starts getting up in the weakening of that crust, it can actually break through and deposit magma, which will cool and solidify, creating these mid-ocean ridges or underwater mountain chains. And finally, a feature that we can predict will be located at a divergent plate boundary are both volcanoes and earthquakes that occur when we have that molten material venting, where the magma is able to rise to the surface. So just understanding how our planet is divided into different lithospheric plates, oceanic and continental crust, really helps us from a human standpoint in predicting where some of these natural disasters can occur and how we can better prepare for those. So here's an image. Give you a second to kind of put this in perspective. These are houses or man-made structures here. This is in a hotspot over Iceland where the North American and Eurasian plate are rifting or tearing apart. So this is that rift that's forming. It's one of the few places on the planet that we can see this on the surface of the land, because as we mentioned, a lot of times that's happening on the ocean floor where those mid-ocean ridges form. Here's another image from Iceland as well, showing me a bridge going across that rift that's connecting the two plates where they're pulling or rifting apart. So that is a divergent plate boundary. Oh, we have one more cool image. This is of the Great Rift Valley that a lot of us are familiar with that term. This starts kind of in the north up by Jordan, but this goes all the way down through East Africa where the continents are rifting or splitting apart. This is the Great Rift Valley, that thin part of the continental crust as these two plates are rifting or pulling apart. And we've spent a fair amount of time in the Rift Valley on the Masai Mara, on the Serengeti, looking at some of the amazing biodiversity that results from the diverse ecosystems created by tectonic plate activity. Okay, so the next type of tectonic plate boundary is convergent. This is where two plates come together. I'm going to give you just about 30 seconds to familiarize yourself with this diagram. There's kind of a lot going on here, and see if you can recall the processes that are occurring, if you could describe the process that's occurring at a convergent plate boundary, and how that leads to the certain geologic features that we see there. So take just about 30 seconds and look at that and see if you can answer those. Well, I'm going to give you a little hint, and it's one of the key vocabulary terms that I want to have in my repertoire if I'm going to explain what's happening at a convergent plate boundary. Remember, where those plates come together, one plate is going to subduct or push underneath the other plate. When that plate subducts, when it pushes underneath this other plate, if this is oceanic crust that's pushing underneath here, when that happens, this oceanic crust is pushed down into the mantle, and that solid earth material melts and becomes magma that can be vented to the surface. Then I can have volcanic eruptions that bring that molten melted material to the surface and deposit it, creating what we call a volcanic island arc. The collision of these plates can also cause earthquakes. The third type of plate boundary is a transform boundary or a transform fault boundary. This is where we have plates grinding past one another in opposite directions, like we see on the coast of California, where I have the North American plate moving one direction and the Pacific plate moving in opposite direction, and that creates friction that over time will be released as an earthquake. So earthquakes are very common because of that buildup of pressure. This is sort of that overview then of all of our planet broken down into its different tectonic plate boundaries. Let's just make sure we can make sense of this based on that review that we just did. So see if you can find on here, well, you can see this is a good example of a spreading zone. And remember, at a spreading zone, at a divergent plate boundary, the main feature I see are those mid-ocean ridges. So this is the mid-Atlantic ridge where those plates diverge, molten material comes up at that seafloor spreading center and is solidified. Well, one of the key things we said happened at a subduction zone were those island arc volcanoes. And notice this, we've got this big belt of where two plates are coming together and one is subducting under the other. So there I have those island arcs. You may have talked about the ring of fire, this ring of intense volcanic and earthquake activity along the rim of the Pacific plate, this huge subduction zone, and that just, it kind of dissects the entire planet in two. So let's do a quick check for understanding and see if you can describe and explain and kind of relating this back to the bigger picture. So remember that these geologic processes have sculpted our planet over time. That's created a lot of ecosystem diversity. When that plate subducted into the mantle, I was recycling earth material. The same atoms that make the same elements that go together to form minerals are constantly being recycled. They're solid and get melted into magma that then comes up on the seafloor and creates a ridge, or is vented through a volcano and creates an island. It just happens over a time span of millions of years. And it's always a really challenging thing for science teachers to try to help our students visualize what that long time frame is going to look like, how long those processes take to happen. Remember, this is going to help us know where valuable mineral resources are located, where I have tectonic plate activity, and I can have minerals from the mantle of the earth be deposited on the surface. Those processes help me predict that location. These resources, because these processes happen not on a human time scale, but a geologic time scale, these mineral resources are present in a finite amount. They are non-renewable. And oftentimes the location of those resources, there's no link between, like, which countries are the most populous or industrialized? Do they have all the minerals? Obviously, the processes that deposit these minerals don't take into account geopolitical boundaries. So countries that have a lot of these resources have a lot of power if they're valuable resources. And that brings in a lot of the environmental science aspect by looking at that and how humans interact with their environment. So let's do a quick check on some of those concepts before we move on to the atmosphere, because we're going to kind of switch gears and go to a new topic here in a second. So this should look familiar to you. It's showing you the Earth's major crustal plates. Just a quick identify the letter. Area where new crust is being created at a divergent boundary. That's letter B. That's that mid-Atlantic ridge we just went over. The location of an island arc formed by subduction. I think my students may have seen this question. You may have as well. And I think they're like, wow, there's only one place that kind of shows islands there. So I have a pretty good chance that that's letter E. Here's another multiple choice question. Scientists are looking at new locations to generate electricity using geothermal energy. Which of the following locations would be the best choice for a geothermal generating plant? So again, here's where you're going to see a little more application of the content that we're reviewing. Remember, Iceland has a lot of geothermal energy. We saw those rifts where the tectonic plates are moving apart, and a lot of geothermal activity and thus geothermal energy there. Now let's go one step further, and this is where we're going to see if we can describe and then explain. So Japan, Indonesia, and the Philippines are examples of volcanic island chains that formed along subduction zones in the Western Pacific. This is the ring of fire we just looked at. Describe what happens when two plates collide along a subduction zone. Remember, one plate pushes underneath the other. They already gave us that term subduction, but I could have used that in my description again. And then I want to explain how the subduction leads to volcanic activity. So remember, when that plate subducts, it goes into the mantle, it melts, and then that is molten material that can rise to the surface or be vented through that volcanic activity. So now we're going to go on to sort of the second half of the lesson for today. We're going to leave the lithosphere and the solid part of the earth and go to the atmosphere. So a quick review on this first learning part is just really kind of what the atmosphere is all about, sort of some of these facts that we need to remember about it. And then we're going to look at how understanding the basic working of the atmosphere will allow us to, guess what, explain some other kind of process. So we have lots of different layers, but I think we really want to focus on the troposphere and stratosphere. When you remind yourself what happens in these different layers, mostly from the air pollution unit, this is really where humans are interacting with the atmosphere. Boy, it seems like there's a lot going on in this graph, so let's kind of break it down. Oh, we have to remember the composition of the atmosphere. That's another essential knowledge statement. And we reviewed that when we did the nitrogen cycle, because remember, the atmosphere is a major sink for nitrogen, and I now am connecting that. Because there is so much nitrogen as a gas in the atmosphere, nitrogen cycles really quickly. Unlike phosphorus, that does not have a gaseous phase. I don't have any phosphorus gas in the atmosphere. Now, what else is this graph showing me? Okay, I got all kinds of axes labels here. My y-axis is temperature. I have another y-axis up here. This is my atmospheric pressure in millibars, and my x-axis is temperature and atmospheric pressure in millibars. It looks like there might be two different labels on my y-axis. They're both altitude, they're just in different units. One is in miles and one is in kilometers. So I really want you to focus on just this little part of what's going on this line down here, and let's just do a quick interpretation, because it's this part of the atmosphere that we're going to live in for the rest of our lesson and try to explain what's going on there. So let's do miles. Maybe that's something you can visualize pretty easily. Whoa, I have to go up pretty far in the troposphere before I even get to the stratosphere. Remember, Denver's a mile-high city. That's 5,280 feet. That's only 1 mile. So let's say that I'm hiking some 14ers in Colorado. They have a lot of 14,000-foot peaks. When I'm climbing a 14,000-foot mountain, I'm about 2.5 miles above sea level. So what I really want to focus on is the fact that as I increase in altitude, as I go from sea level up to the top of a mountain, the temperature decreases. It gets colder. So hold that thought. As I go from sea level up to the top of the mountain and increase altitude, I decrease temperature. That's really what we want to focus on. It's the essential knowledge that we're going to have to use to explain and describe other processes. Well, let's see what those other processes are. Global wind patterns. We're now moving into this idea of how weather and climate patterns are created, and that I can apply to explaining a really big issue in environmental science, a really big concept. So boy, it seems like there's a lot going on here as well. We have sunlight striking the surface of the earth and it's being heated. And although there's all these different arrows, let's just kind of focus in on this one little part of the graph, and just everything else is just repeating. There's just a pattern that's happening here. And in your textbook, you may see diagrams like this that show you more complexity, maybe more labels as to the type of air masses. Just don't even go down all of those little facts. We want to be able to describe and explain a big concept. So that's where we really want to dig in here. Don't get too deep in the weeds on a lot of those facts. Not that they're not important, but because we're reviewing and we know what we're going to be asked to do, and really focusing in on the describing and explaining. So sunlight strikes the surface of the earth and it heats the surface of the earth. And that air mass, as it's warm, it's got a lot of space between the molecules. So at the surface of the earth, that air mass, as those molecules of air get heated. When I use the term air mass, think about it like a big block of air. That's what I want you to visualize. So as the surface of the earth is heated, that big block of air right over the surface of the earth is heated. And when I heat up the air mass, that big box of air, those air molecules move further apart. They spread out and they become less dense. There is a very small mass of air molecules in the same volume. Well, remember what I told you to carry forward from that complex temperature altitude graph that we just looked at? As that air mass, because it's warm and less dense, those molecules are really far apart, that less dense air mass is going to start to rise. Well, what happens when we go from sea level to the top of the mountain? It gets colder. And as that air mass, as that box of air cools, those molecules start losing their kinetic energy and they really close together and become a lot more dense. And as they become more dense, then they're going to fall or sink or descend. Well, what do I create when I have air masses that warm, become less dense, rise, and then they cool, become more dense and sink? I create global wind patterns. And that you need to be able to just describe that process, not a lot of nitty-gritty about the names of all those different air masses. So let's dig a little bit deeper then into this idea of global wind patterns. So hopefully you're pretty good with this rising and sinking of air mass creating wind patterns. These wind patterns, you might remember, are big conveyor belts to transfer heat, but they also transfer moisture. What do I have when I have temperature and precipitation? I have climate patterns, and climate patterns determine patterns of biome distribution. So this is what I'm getting at. In the big scheme of things, I'm going to have to be able to describe and explain these processes so I can then relate it and step back and relate it to a broader environmental issue. So we're getting into reviewing enough content that we're really starting to connect a lot of these different topics into a very rich description and explanation. So let's go back to our little model of these this warm air mass with low density. Well, picture a little water molecule in there. When I have a low density warm air mass, there's all kinds of space between those water molecules or between those air molecules for little water molecules to slip in. It doesn't work quite that way with a cold air mass where the molecules are really close together and very dense. There's just not room for those little water vapor molecules to slip in there. So now we want to relate not only temperature and altitude, but what happens also to that air mass as it's rising and cooling, and the air mass gets more dense and it can't hold as much water. Now we're relating this to the hydrologic cycle. As that warm air mass that can hold all kinds of water rises and cools, it can't hold as much precipitation. We get condensation, or as much moisture, we get condensation, and all that moisture falls as precipitation. So if I look at this graph, I can see that there is a direct relationship between temperature and the moisture holding capacity. The warmer the air mass is, the warmer the air mass is, the more moisture it can hold. So at the surface, when that air mass is really warm, it can hold a lot of moisture, but as it rises and becomes more dense, it can't hold as much water vapor, and that falls as precipitation. So I'm creating wind patterns, but I'm also creating patterns in precipitation by the movement of these air masses as well. So let's see if we can take a step back for a minute and go back to how that Earth surface got heated to begin with, and why isn't every place on the Earth the same then? If we always have the surface of the Earth heating an air mass, and that air mass rising and letting go of its moisture, and we create those patterns or bands, why don't we just have the same pattern or band all over the planet? And that's where we need to review this concept of solar insolation. Remember, that stands for incoming solar radiation. And that when I taught this to my students, the way I explained it, and that's what this diagram is kind of showing down here, is that if our Earth were a cube, we wouldn't have to talk about solar insolation because the sun would always be striking the Earth at the same angle, whether it was the North Pole, the equator, or the South Pole. I have the same amount of incoming solar radiation. But obviously our planet is not a cube, it's this beautiful sphere. So as I curve up to the North Pole, and get my curvature to the North Pole here, when I have that sunlight coming in from solar radiation from the sun, it's not striking straight on. At the equator, and remember this is 0 degrees degrees latitude, I can have 90 degrees north or 90 degrees south. When I move from the equator, 0 degrees latitude, and I get the curvature of the Earth, that sunlight is striking at an oblique angle. And so the same amount of solar energy at the equator is spread over a pretty concentrated small surface area, but because it's striking at a curvature and that sunlight has to come in and hit at that angle, the same amount of energy is spread over a much larger surface area as I move toward the pole. So that's starting to make a connection to me between where biomes are located and the climate that it has. Let's do a little guided practice on this quick. So here's a beautiful NASA image that shows me the Earth with a unit of net radiation represented in different colors across this continuum. And my unit here is watts per meter squared. So in other words, how much energy per square meter of Earth's surface. And I can see, well, I'll let you decide how you're going to say that. Describe the relationship between latitude and radiation per unit area. And next I want you to be able to explain the pattern. Remember, we're really focusing on describe, explain using some type of model. So once you've simply, the easier part is maybe describing what happens, that identify, interpret, that Dr. Sullivan and I have been working on with you. Next, you have to be able to explain solar insolation. So the relationship is there's an increased amount of solar radiation at 0 degrees latitude, or the greatest amount at 0 degrees, and that it decreases as you increase latitude. You need to be a little bit careful here because it's said to describe the relationship between latitude and radiation per unit area. I need to make sure that I'm explicit, that I understand. If I simply say the equator and the pole, I really haven't tied in that idea of latitude. So I need to know that the equator is 0 latitude. I could simply say that as I increase latitude, I decrease the solar energy per unit area. That's basically what I said here. Just make sure that you get that the equator is 0 degrees and the north and south pole are each 90 degrees. And I have that pattern repeat as I move away from the equator. Explaining that process is solar insolation. The amount of solar radiation that hits the equator directly, all that energy is absorbed over a small area, and at high latitudes, that same amount of energy is spread out over a larger unit area. That's why it's important that we look at our unit, the amount of energy per unit area. So we're going to now go one step further. Now that we understand this idea of how winds are created and how winds transfer both heat and moisture, and that varies because different amounts of different places on the surface of the Earth get different amounts of incoming solar radiation. So we tie that all together. Now we want to take a look at how that all relates to the seasons on the Earth. So I'm going to show you a quick video clip that explains it, and then we'll look at that still image and walk through what's happening.
Earth remains tilted in the same direction all year round as we orbit the sun. But that means the sun's light shines differently on Earth at different times of the year. Let's look at Earth when it's winter in the northern hemisphere. Observe how the North Pole tips away from the sun. This means that sunlight strikes the northern hemisphere at a shallow angle for a short period of time. This is why winter weather is generally cool with short days and months. As Earth orbits the sun, we move towards spring in the northern hemisphere. Now Earth is tilted neither toward nor away from the sun, as day and night are about equal in length. As we make our way to the summer months, notice that Earth is still tilted in the same direction, only now on the other side of our orbit. The North Pole is tipping toward the sun. Sunlight strikes the northern hemisphere more directly, and the sun stays in the sky for a longer time. Compared to winter, summer days are warmer. The sun stays in the sky much longer. Notice too that while it's summer in the northern hemisphere, it's winter in the southern hemisphere. Because of Earth's tilt, the seasons aren't reversed. We observed how Earth's tilt creates the different seasons throughout the year. How does this affect life? Plant life and other photosynthesizers, we call them primary producers, depend on sunlight. They respond to the changes in the seasons. Earth orbiting satellites measure the amount of carbon dioxide absorbed by these primary producers. Bright regions on this map show where they devour the most carbon dioxide, turning light from the sun into oxygen and natural sugars. In spring, when sunshine strikes the cold waters of the North Pacific, productivity skyrockets. Phytoplankton and other microscopic photosynthesizers form the base of the ocean movement, and all ocean life responds to changes in seasons. On land, forests grow green during spring, brightening the continents. During winter, continents in this field turn dark from a lack of photosynthesis.
Oh, what a beautiful job in kind of bringing together a lot of those ideas. I think we maybe looked at an image when we reviewed the carbon cycle about changes in carbon dioxide concentration from northern hemisphere to southern hemisphere in different seasons. Now we can explain why that is. We're really starting to connect different ideas, and that's often what they want us to do in our free response, is draw and bring together a lot of different concepts. So here's the simple static cartoon diagram that again shows me. You can see it in the animation very nicely, the areas that are getting the greatest amount of sun and the areas that are shaded. So remember that during the summer, when the southern hemisphere is during our summer in the northern hemisphere, when the southern hemisphere is tipped away, the South Pole could have almost 24 hours of darkness. The sun may never quite get over the horizon, but just the reverse is true later. Now the the North Pole is up in almost complete darkness, and the southern hemisphere has almost 24 hours of daylight. So the last big idea we want to take a look at is how the oceans influence climate by absorbing different amounts of solar radiation. And I'm just going to present the big idea of ocean circulation, and Dr. Sowell's really going to apply some of this little bit of content that we review here. So let's take a look at how oceans influence climate by absorbing solar radiation and releasing heat, another piece of the puzzle of global circulation.
Earth is the water planet. Although 40% of Earth's population lives within or near coastal regions, the ocean impacts people everywhere. Most of Earth's water is stored in the ocean, a driving force for weather and climate. The Earth's surface is warmed unevenly by the sun. Heat, a form of energy, helps drive ocean and atmospheric circulation. The ocean absorbs and stores more heat than the atmosphere. Both the atmosphere and ocean move heat. The atmosphere does this quickly, the ocean slowly. At the ocean's surface, winds drive currents. Multiple forces keep the global ocean conveyor belt, or thermohaline circulation, in perpetual motion. Below the surface, deeper currents.
We're not going to go into the deep currents, but hopefully that was a good review for you about the idea that the oceans and the atmosphere can both absorb heat. Water has a very high heat capacity. When heated, it tends to really hold on to that heat. So we have heat and moisture being transferred by atmospheric currents. We have heat being transferred by ocean currents, and you're going to pick up with that idea tomorrow or on Monday in the next lecture with Dr. Sowell. So let's go back. We have one other aspect of weather and climate that we need to take a look at, and it's how the Earth's geography influences that. So I'm going to just ask you to quickly recall what we went over about how when an air mass rises and it gets cooler, it loses its water vapor capacity, condensation occurs, and that falls as precipitation. That description of that process helps me explain the rain shadow effect, and it helps me really understand another aspect of how different climate patterns are distributed around our planet. So here's a simple cartoon image of the rain shadow effect, but I think we're at the point where we can look at this in a little bit broader, more realistic context. So here's a beautiful physical map of the state of Washington. Just as a reminder, this is Puget Sound. We're up here in the Pacific Northwest, in the very northern corner of the United States, and I have the Cascade Mountains there. So I want to see if you can visualize, based on the cartoon image that we just looked at, what's happening here. So I have these prevailing winds that bring this moist air mass in from the Pacific Ocean, and as that air mass rises to go over the Cascade Mountains, it cools, it loses its ability to hold water. You don't even have to quite go that far. You can just say the air mass rises, cools, and drops the rain as precipitation. It can't hold as much water. And then on this side, you may have learned this as the windward and leeward side of the mountains. Notice that I've got a very different, I can tell by looking at the map here that I have a very different ecosystem. That it looks like there's a lot of vegetation here. This looks like there's almost no vegetation. Well, let's relate that to a map that shows me annual precipitation in the state of Washington. You probably realize that Seattle is famed for the large amount of precipitation it gets. Look at in these areas where the greatest amounts of precipitation, even in this like hot pink region, I have 100 to 140 inches of rain per year. When you're done here, go and check in your local area how much rain you get per year. Obviously, some of you live in this region, but just as a comparison so that you have an idea of how to compare it to how much rain you get. That's a lot of rainfall. But now look over here in that area on the leeward side of the mountain. Here's my Cascade Mountains where all that air mass is rising, dropping precipitation, and then continuing on down the other side of the mountain. Look at the dramatic difference. I went from 150 inches of rain a year to less than 10 inches of rain a year in really not that long geographic distance from point A to point B. So the rain shadow effect helps me understand the geography of a region, helps me explain a lot about its climate as well. Here's another really good example, just a little bit further south of Washington along the Pacific Ocean. Here are the Sierra Nevada mountains in California, the San Joaquin Valley where a lot of our food is grown. And then look at on the other side of this, I have all these this forested range in this area. And then on the other side of that, I have the Mojave Desert and Death Valley. So geography, the location of mountains, has a big influence on climate and weather patterns. So let's do a quick check for understanding of a couple of the concepts that we went through in the second half of the lesson, where we looked at atmosphere and how that creates weather and climate patterns. Which of the following causes the air to rise into the atmosphere in the areas labeled A, B, and C on the diagram? And the correct answer is C, warm, moist air that is less dense than the surrounding air. Remember when we looked at that first image that looked kind of like this, I just focused in on one area where that was happening. Remember this, we're seeing patterns here to this process. And that is what is determining the location of biomes. Why do I have tropical rainforests at the equator? Because I'm constantly circulating that warm air and dumping that precipitation on a daily basis. If you chose letter B, which may have been one of the most selected incorrect answers, this is something we're going to address in a little more detail later. We have, guess what, another model that I'm looking at that's showing me some data that I have to use that model or representation to describe or explain a process. So I have the relative solar energy at two different locations throughout the year. Let's make sense of our graph. I show the months from January to December. So I'm looking at change in seasons and the relative amount of solar energy, that incoming solar radiation or solar insolation. I can see that location 1 tends to have about a flat line. There doesn't seem to be a whole lot of difference in the amount of incoming solar radiation throughout the year. And location 2 has a very dramatic change in the amount of solar radiation. And it looks like I have seasons of the year where there are times when there's a small amount and times where there's a peak amount of solar radiation. So take a look at that multiple choice question. Which of the following can be concluded about the latitudes of the two locations? And hopefully you picked letter B as the correct answer. Location 1 is closest to the equator. I know that location 2 is most likely the northern hemisphere because it's during the northern hemisphere months of June, July, and August that we are tilted towards the sun and would be experiencing the greatest amount of incoming solar radiation. We have a little bit of guided practice. Whoa, looking at another diagram. Go figure. So here I have the ocean. Here I have city A. Here I have city B. Identify the city that receives the greatest amount of precipitation. So this is easy. We don't have to explain anything yet. I'm going to be a little careful. I guess they could give us a diagram where I had a wind coming in from the other direction. It seems like all the rain shadow effect diagrams that we look at kind of have that wind going from left to right or from west to east. So I have to be a little bit careful there. Obviously, the greatest precipitation is going to be city A. And the explanation for that is that air mass that blows in off the ocean has a lot of moisture, has a lot of water. As the air mass rises to ascend or go over the mountains, it cools and the water falls as precipitation. It's really the greatest amount of detail that I need to provide there. So just a quick debrief and summary. Why do we care? Remember that in the big scheme of things, understanding how solar radiation strikes the surface of the earth, how air masses are heated, creating wind patterns that transfer heat and moisture, and that the ocean can hold a lot of heat and transfer that heat. All of this helps us explain patterns of biomes, which are really different kinds of ecosystems, that ecosystem diversity. Just so that you make sure and see all the essential knowledge statements from the second half of the lesson on the atmosphere. These are the first things that we looked at when we looked at gases in the atmosphere and the relationship between temperature and altitude. We looked at how global winds are created and those patterns. And then we have all of these essential knowledge statements that really dig into this solar insolation and the tilt of the earth and different seasons. So in terms of AP exam practice, this is no homework Friday. Woo! Dr. Sowell and I feel like you guys have been working so hard. We're halfway through the content. You've really been digging in and practicing a lot of FRQs. And like I said, there's not a super good experimental design or solutions that relate directly to this content, but we're going to use all of this content in the next couple of lessons. So don't worry, you'll come back and get some more FRQ practice homework. That being said, I would like just why doesn't everybody try to get outside this weekend? I know that it's hard. We know that this is hard for you reviewing for AP exams kind of on your own. We're here for you. We hope that you're getting a lot out of your virtual lessons. We wish we could answer questions for you, but just take a step back this weekend and get outside, spend some time with your family if you're not too sick of them yet. Maybe go pick up some litter by yourself somewhere, but then maybe on Sunday evening just come back and say, okay, I'm going to take a couple minutes to review what we went through in those first 3 units and halfway through number 4, and then we'll see you next week. So have a great rest of your day. Thanks for watching. Make good choices. See you next time, guys. Hola.
Hello, everybody. Welcome to AP Environmental Science Review for the exam coming up. All right. So my name is Dr. Sowell, and I teach APES here in Jacksonville, Florida, at Darnell Middle High School. So just as one more reminder, remember here's our exam date, the 18th, and here are the descriptions of our 2 FRQs that are going to be on the exam. So here's where we're going today. Our goal today is to finish up the Unit 4, and Ms. Fassler did half of that unit the other day, and I'm going to do the second half today. So we're going to do 2 topics from that unit, 4.2 and 4.3, all about soil. So we'll do the soil composition, properties, and erosion, formation, all those things about soil. And then we're going to jump to 4.6 on watersheds, and then end with El Nino and La Nina. We're also going to tackle a few times during today's lesson some skills associated with practice number 4 on scientific experiments. So here's what Unit 4 looks like as a whole. So Ms. Fassler did a good chunk of this the other day, and I'm going to hit again the 2 topics on soil, then watersheds, and El Nino. But I want to point out in the box that talks about some skills that might be useful to understanding these topics, the ones about soil were identifying, describing aspects of research method, design, and or measure used. And I'll say this several times today, but we're going to look at a few quantifiable tests that you can do on soil. And because soil testing is so accessible and understandable for us as teachers and for you as students, that is something that is very easy to incorporate into an experimental design question, for example. So we'll try to play with those a little bit today. All right, so what do you need to know? For 4.2, by the end of the section, you should be able to describe the characteristics and formation. So how does soil form? What are its characteristics? So to get there, we're going to describe the formation of soil, describe the horizons of mature soils, late successionary soils. We're going to describe what erosion is, and then we're going to look at the impact of that on water quality. All right, so let's just start by what is soil? So soil is a huge natural resource for us. It's this unique mix of organic and inorganic stuff that forms this very thin layer all over the earth. And I also like to think of it like this recipe, this gorgeously rich, unique recipe that kind of takes ingredients from the lithosphere and the biosphere and hydrosphere and atmosphere, puts it all together into something really kind of unique, which is soil. So I want you to take 10 seconds or so, and could you in your head think of a few ecosystem services that soil provides? So you may have thought initially about agriculture, and that is a huge part of why soil is important to us as humans. It's a place where we grow our crops, a lot of our crops, but there's also some other ones as well. So think about cultural ecosystem services, using it for pottery or for housing or for paints or as inspiration for songs and poems. So just don't forget that cultural ecosystem service, that cultural category. And so soil is just an example of that as well. So I'm going to start with a short video clip from the Soil Science Society of America, and this is about some of those other ecosystem services of soil and why soil is important. I think it's good to foreground this conversation before we get into the details. Just as an aside, the Soil Science Society of America is a great website for review on soils, and their YouTube channel has tons of really short videos like the one we're getting ready to watch, so I highly recommend it. All right, let's take a look at this.
In the U.S., whether you live in a house, condo, or an apartment, your home is connected to the soil in more ways than you know. Your school, the building where you work, the stores you shop in, all of them are built on soil, and often with it. It's easy to see how a brick or a stucco building is made of soil. Bricks and stucco are made from a mixture of sand and clay. But even wood frame buildings are connected to soil. The lumber came from trees grown in soil, and the cement foundation came from elements of soil. Worldwide, about half the world's population lives in houses made of soil, from adobe houses here in America to brick houses in Europe to mud houses in Africa. And all buildings are sitting on, you guessed it, soil. Building foundations need to be on stable and strong soils. Soils range in strength from being able to support a skyscraper to not being able to support the weight of a human. If the soil under a building is not stable, the foundation of the building could crack, or worse, the building could fall. Soil plays a major role in cleaning our wastewater too. If you live in the countryside, your septic system relies on soil to help clean the water. Septic tanks slowly release water into the surrounding soil and utilize the soil's natural ability to clean water before it returns to the groundwater system. Leaching trenches, leach fields, or drain fields have been used for years to collect and treat the effluent from septic systems. These systems have also been used to capture the rainwater flowing from roofs into gutters and across properties. The design allows water to seep into the ground rather than streaming onto city streets and contributing to runoff problems and pollution. Cities depend on stormwater systems to manage rainfall and snowmelt, and these systems depend on soils too. Cities are building more green space, rain gardens, and green infrastructure to direct more of the precipitation into these natural cleansing systems and reduce the burden on stormwater systems. Rain gardens collect water, and as the water moves down through the soil, it's cleaned. Green infrastructures, including green roofs, bioswales, and more, also help soil in its job of cleaning water. Soils are the foundation of our built environment and our life support systems. Not only does soil support our infrastructure, soil support life.
So it's just a nice place to start a conversation about soil, thinking about things other than a place for seeds to plant. All right, so what is soil made of? The first and the most majority of it is these mineral particles, pieces of rock, little tiny pieces of rock, the sand, silt, and clay. That makes about 45% of soil on average. Then we've got some water and air, that's no surprise. And then we've got all the organic material, things that decompose into the soil. So we've got this abiotic and biotic mix. But not all soils are the same. I live here in Florida, and if I go out to the beach a couple miles from here, this is what I would see, really, really sandy soils. If I just drive a couple hours north into South Georgia, I get this really beautiful, rich soil that's high in clay. So there's lots of variety in terms of what soils look like and how they behave and their properties. So where did this come from? Why do we have such a diversity of soil types? It comes from the fact that there are 5 formation factors, and those factors change from location to location. We're not going to go into each 5 in depth. We are going to mention them because soil formation is a key part of this topic. So the first factor is parent material. I said before that about 45% of soil is tiny pieces of rock, that sand, silt, and clay. And so the parent material is the rock that soil came from. And then we've got time. I will remind you of the conversation we had on primary succession a few lessons ago. That really emphasized the fact that over time, succession happens in a community, and over time, that depth of soil changes as well. So there's a big difference between early successional young soils and late successional mature soils. So time matters. Organisms, lots of stuff living in the ground, and those things have to decompose that organic matter. Climate makes sense. What kind of climates might accelerate that decomposition, or what type of climates might accelerate erosion? And then finally, topography. This is a pretty simple one in terms of the slope of the terrain of the land. Think about a hill and a valley. The soil on the hill might be a little different than the soil on the valley just because of the way that water and sediment flows downhill by gravity. So these are the 5 factors, and every location has a different mix of these 5 factors. So let's start briefly to talk about the parent material. So here we've got a rock that's being broken up. We've got a rock here that's being weathered away by waves, it looks like. And this rock is being weathered away chemically by acids secreted by these lichens. So soil are formed when parent material, the rock, is weathered, transported, and deposited. And weathering just means breaking up into smaller pieces. And then because the soil comes from the rock, it's like its parent. And so parents provide their characteristics and traits to their offspring, kind of similar to the soil. For example, soil rich in, or rocks rich in calcium carbonate, like limestone, the soil that may form from that rock might be high in calcium, for example. So again, reminder about primary succession conversation we had before. If you want more details about how soil forms in a location where there's no soil there, how the soil even start to get there, that's the conversation we had before about primary succession and pioneer species. All right, so then we've got good old time. And again, as succession happens, soil gets more and more mature and more deep. So over here, when there's just a little tiny bit of grass and lichen and moss, the soil is really thin here, mainly rock. But as we go over the course of several hundred years, maybe, we get to a situation where the soil is really deep. And in fact, it has distinct layers. You can see here O, A, B, and C. These horizons are unique and different. They didn't exist back here. So let's talk about these horizons a little bit more. So all of the horizons together is called a soil profile. And then the layers are OABC, OABC, OABC. I might get to chant that a few times and kind of get it in our head, OABC. So let's go through these horizons and give a brief description of what's going on in each. All right, so the top horizon is called the O horizon. This is where we have leaf litter and decomposing detritus, things that are decomposing into the soil. And at the bottom of the O horizon and into the A horizon, you're going to see something like called humus, not hummus. Hummus is a chickpea and tahini dip from the Middle Eastern countries. So to my Middle Eastern friends, Arabic friends. But yeah, this is not hummus, this is humus. And humus is really rich, fertile, decomposed material that adds a lot of fertility to soil. So then we get into the A horizon. And the A horizon is where this decomposing stuff mixes in with that sand, silt, and clay. So now we have something that some farmers might call topsoil because that's where a lot of roots might exist. But this is a mixture of that organic material and the sand, silt, and clay. Below that, we have the E horizon. Sometimes E is not always there because it's created by leaching. Remember, leaching is when water flows through the soil and takes something from one location and brings it to another. So if there's not a lot of leaching happening, you may not have an E horizon. But if you do, it is heavily leached. It has had a lot of things removed from it. Those things land down here in the B horizon. This is where things accumulate like clay and nutrients that are leached from above layers. And then finally, get to the C horizon. This is where we see weathered pieces of rock right above the solid bedrock, the parent material. So O, A, E, B, C. Here's an example of one. You see the O horizon, all these fallen leaves. The A horizon is topsoil. It's where the decomposed material is mixing in with the sand, silt, and clay, where the roots are kind of at. Then we have this B horizon down here. Notice there's no E. And then we've got C, the broken gravel and rocks. And then we've got the bedrock. So I mentioned before organisms. Organisms are a huge part of soil. Now, clearly we think of big things like earthworms and grubs and moles. They are hugely important to soil because one of the things they do is as they burrow and tunnel through the soil, they aerate the soil. They help to make spaces in the soil for air and water to enter. And then we have lots of smaller organisms, bacteria, fungi, nematodes, mites, a lot of other organisms in there as well that are feeding off of the organic material in the soil. But don't remember, that's their habitat. The habitat for this earthworm is this soil. So when we lose soil through erosion or maybe we pave over it for a parking lot, we are altering or getting rid of the habitat for these organisms. So I want to focus a little bit more on the bacteria. So this is a great place to tie back in biogeochemical cycles, in particular the nitrogen cycle, because in the soil are the bacteria that really are the driving force behind a lot of the nitrogen cycle. So for example, in the roots of legumes, we have these nodules, and inside those nodules are bacteria, nitrogen-fixing bacteria that can turn atmospheric nitrogen into a form that plants can use, like ammonia. But it's not just those nitrogen-fixing bacteria. There's denitrifying bacteria, nitrifying bacteria. There's lots of other species of bacteria that live in the soil that drive the nitrogen cycle. So another huge reason why soil is important. So we know how soil gets there, but it can also leave as well. And it can naturally happen through wind or water. But there are some things that we can do, like tillage in a field, that may accelerate that movement of wind and movement of water that's moving those soils away. So losing the soil or moving the soil from one location to the other is erosion. Why do we care? Sometimes that might create sediment pollution in waterways, increasing the turbidity, reducing the ability of photosynthesis to happen, or getting clogged in the gills of organisms. So erosion, you need to understand in terms of just what is it? Has it naturally happened by wind and by water? But also what are some anthropogenic forces that push more erosion to happen? And we'll talk a lot more about that when we get to our conversations of sustainable agriculture practices. Roots matter. Roots matter. In terms of erosion, nothing stops erosion like a good set of roots. So if you look at these pictures here, notice how tight of a grip these roots have on the soil. So if there's a big wind or a big flow of water, it's going to reduce the erosion because the soil is kind of grabbed onto by these roots. But if we do something like overgraze a plot of land and we reduce that vegetation and the roots go away, this area is more prone to erosion. And you can do a simple experiment like this. You can take some bottles and fill them halfway with soil and then add different amounts of leaf litter and grass. And notice that this particular jar where the grass is growing and there's lots of these roots grabbing onto the soil, the water coming out is much clearer, so obviously less erosion. Just don't forget the power of the roots to control erosion. Another ecosystem service that was mentioned in the video was cleaning our water. So the layers of soil kind of act like millions and millions of coffee filters that clean and filter the water as it goes through the soil. So if this is my house and I have a well that goes down into the aquifer to draw up drinking water for me, it's beneficial that it has gone through all these layers of soil before I use it. So a huge ecosystem service for us. All right, so let's go into 4.3. So this is composition and properties of soil. So 4.2 was where's the soil come from? What's it about? Now we're going to look at different types of soil and how their composition will alter their physical and chemical properties. So after here, you should be able to describe similarities and differences between properties of different soil types. So to get to that goal, we're going to describe the water holding capacity of soil, describe porosity and permeability, describe how to use the soil triangle, and then how do we use the results of all of those things to inform human decisions, things about agriculture or land use, for example. All right, so I mentioned before sand, silt, and clay. These are the three mineral particles of soil, the tiny, tiny pieces of rock. And you do need to know those sizes. Sand is really big, silt is insanely smaller than that, and clay is even insanely smaller than that. So an individual sand grain you can feel between your fingers. It's like feeling a grain of salt. You can actually see it, and you can feel it. You get all the way down to clay, an individual clay particle is invisible to the naked eye. You have to use some kind of magnifying device to see it. So the size of the mineral particles and their relative portion to each other in a soil sample will change how that soil behaves. So let's take a look at the soil triangle. So I want you to imagine that you went outside and you took some soil and you put it in a jar of water and you shook it really hard for a few minutes and then just set it down. If you didn't disturb that jar and came back maybe 24 hours later, you would notice that the soil particles have sorted themselves by size, with the heavier particles like sand being at the bottom, then silt, and then clay. Well, I could then take a ruler and measure the different amounts of sand, silt, and clay and generate a percentage. So let's say that, for example, this one has 21% clay, 66% sand, and 13% silt. Well, soil scientists use those percentages to give the soil a name. So let's just say that this soil sample had 99% clay. Well, it'd be called clay. And if I had 97% silt, it'd be called silt. But that's not too common. A lot of times we'll see a combination of both. So we use the soil triangle and we use the percentages of sand, silt, and clay to come up with what is the title or the name of that particular soil texture. So let's start with clay, 21%. So to read the soil triangle, you find the side that says clay, and you'll notice that there's a little arrow in this diagram pointing to the horizontal lines. Sometimes there won't be an arrow, but the numbers here will be tilted in the direction that you read. So for clay being 21%, that's where my clay is. So there's 21% clay, 66% sand is being read up this way, and then finally 13% silt. So this type of soil is called sandy clay. All right, let's practice it again. Take a few seconds and see if you can figure out where this one's going to be, what the name of the soil is. So we've got 7% clay down here, 15% sand here, and 78% silt. So we have silty loam. So you definitely need to know how to use a soil triangle. It's a great example of a visual representation or a model that we can use to inform our decisions. So you'll notice a lot of things in the middle have the word loam on it. Loam is a combination of sand, silt, and clay that's typically pretty productive for agricultural use. You can grow things in pure sand or pure silt or pure clay. However, you may have to add amendments to the soil to make it useful for plants, especially crops. But the loam has a combination of all three that make it more beneficial sometimes. All right, so let's talk about why. Why is loam unique in terms of its ability to grow crops better than others? So it's really because of porosity, permeability, and fertility. So let's read the essential knowledge statement here. It says the particle size and composition of each soil horizon can affect porosity, permeability, and fertility. So let's look at how the distribution of sand, silt, and clay affect these three things. Let's start with porosity. Porosity is just the amount of space between the particles of soil, between those mineral particles. So if we look at this sample on the far left, there's no space between them. So there's zero porosity. And because there's zero porosity, nothing's getting through there. It's impermeable. As opposed to the one on the far right here, where there's lots of spaces in between particles. Why are those spaces important? Because it provides a place for air and a place for water. Plants and organisms need both of those things in order to be productive in soil. And clearly, this would be an example of an aquifer, a place in groundwater where we might draw drinking water. So that's porosity. Porosity is how much of the soil is air or is space. What percentage of that soil is open space? As opposed to permeability, which is a rate. This is simply how quickly does water fly through the soil. So you can see here, water passing through sand is going to act differently than water passing through clay. The general rule of thumb is sand is much more permeable than clay. If I had a handful of sand and I poured some water on top of that sand, it would run right through it. It's highly permeable. If I had another handful of clay and poured water onto it, it may sit there for weeks, months, and not leak through. So it's much less permeable. So that's the rule of thumb for permeability. Why do we care about that? Well, coarse textured soils that are high in sand have excellent drainage because of this high permeability. So water is going to flow freely through them. As opposed to fine textured soil, which is high in clay, and have poor drainage because of lower permeability. So think about what we might line the bottom of a landfill with, or the bottom of a pond with. We would typically line it in clay because it's impermeable. You wouldn't want to put sand at the bottom of a landfill because the leachate would go right through it into our groundwater system. So there is some land use and agricultural decisions decisions that are based on understanding porosity and permeability. So for example, irrigation. Let's say I'm using an irrigation, a little drip irrigation practice here. If I had a lot of clay, perhaps the water will kind of stay at the surface and not really go through, and perhaps I might even waterlog my roots here, which might not be good. As opposed to sand, in which the water might just keep on trucking, fly right by the roots, and the roots don't have enough time to grab onto it. Where loam is this kind of Goldilocks sweet spot where the water does flow down, but it does flow through really quickly. It's not super permeable. So again, understanding porosity and permeability can affect land use and agricultural decisions, especially about irrigation. Now fertility. Fertility changes from soil type to soil type to soil type. Obviously, the amount of decomposing material from the O layer into the A layer, that development of that humus or the organic material, that's going to affect the fertility, the amount of potential fertility in the soil. But another thing that happens is clay actually will grab onto those nutrients and hold them for a while so that the roots have access to them. With no clay there, the nutrients will sometimes get leached right out of the soil and the roots won't have time to grab them. But clay acts like a little hand-holding mechanism that holds onto those nutrients for a little while. That's called the cation exchange capacity. Fancy phrase that just means clay particles help to store the nutrients within the soil, making them more accessible to plants. So it's the nutrient holding capacity. So you should already be thinking on that soil triangle, the amount of clay differs, that may affect that soil's ability to grab onto nutrients. So let's take a little minute 47 clip here explaining that.
Not all soils are created equal, and if it weren't for chemistry, we wouldn't be able to grow many crops here, nor here, nor here. It's like this. Soils are composed of sand, silt, clay, and organic matter. Some have more sand, others more clay. Each soil's unique blend determines its color, texture, and storage capacity for nutritious chemicals. Although incredibly small, nutrients still need their space. And by space, we mean the area surrounding the soil's tiny particles. Keep in mind that surface area is not the same as particle size. For example, clay particles are tiny compared to sand, but they have more than 1,000 times as much external surface area as the particles in an equal volume of sand. However, if a nutrient just sits there unattached, it will likely leach out from the soil in grains and will not be available for plants. Remember that time when you rubbed a balloon on your best friend's hair and you stuck it to a wall? Well, a similar phenomenon occurs in the soil. Through their electrostatic energy, nutrients cling on to clay particle surfaces. Nutrients like calcium, magnesium, potassium, and ammonium are all positively charged chemicals, or cations. And as it turns out, most clay particles and organic matter in soil are negatively charged. So, many nutrients are positive, and particles are negative. Perfect. In chemistry, as in romance, opposites attract. Good. No more leaching.
All right, so that's cation exchange capacity. How much a particular soil type has the ability to retain nutrients and not let them get leached out. So that's just one type of test that we could do and use in an experiment. So we could test porosity, we could test permeability, salinity, how much salt is in the soil, pH, how much organic material, the type of soil, the amount of water in the soil, how much the soil has been compacted by things like animal hoofs or foot traffic or machines. So we can do a lot of tests on these soils, and those tests can be used within scientific experiments. And in fact, one of the statements from the curriculum guide says there are a variety of methods to test the chemical, physical, and biological properties of soil that can aid in a variety of decisions, such as irrigation and fertilizer. All right, so now let's move from soil into watersheds. And this is a pretty quick topic because you really just need to understand what a watershed is and how it operates. So we're going to describe the characteristics of a watershed. To do that, we're going to define it. What's a watershed? Describe how one watershed might be different from another, and finally explain how the concept of a watershed can inform decisions about pollution and land use. So simply put, watershed is an area of land that drains into a body of water, like a stream, lake, river, or well. So you can see here that you almost have this bowl-shaped area of land, high mountain ridges all around there. So if I'm a drop of water falling from the sky right here, and I land right here, eventually I'm either going to move because of runoff, surface runoff, or maybe go into the groundwater and move, but eventually I'm going to make it down into this river. So all of this land, this might be hundreds and hundreds of miles, or it might be really small, like a couple of meters, depends on the scale that you're looking at. But this is an entire watershed. All the water that falls onto this body of land is either going to run off of the surface, go into a tributary, or go down below into the groundwater, and eventually make it into the same location. So if we have multiple watersheds next to each other, they create a series of watersheds. So we might have a watershed here, and a watershed here, because if a drop of rain lands right here, it's going to flow this way. But if a water droplet lands right here, it's going to flow this way. So the things that divide watersheds are divides. And you can think about how watersheds might behave differently if they're have a bigger slope, if they're steeper, the type of vegetation you might have there, how the soil types within a watershed might affect how that water moves. But in essence, we need to understand that all the water in a watershed moves to a central location, either at the surface or in the ground, and that watersheds are divided by divides. And this is a great picture of all the major watersheds in the United States. And this big giant pink one here is a great representation of the Mississippi watershed, with all of that water eventually making its way down into the Gulf of Mexico here. So let's talk about me for a minute. So this is where I live. I live up in Jacksonville in the northeast part of Florida. And so we have a very large river called the St. Johns River that flows north up through the state, and then takes a sharp right here where I live in Jacksonville into the Atlantic Ocean. Well, all of this light color here is the watershed for the St. Johns River. That means any water that lands anywhere in this area will eventually make it into the St. Johns River. But if we zoom in a little bit, we can see that here's some tributaries, little creeks that run into the river. So if I'm in this spot right here, not only am I part of this watershed going into this creek, but I'm also part of the watershed of the St. John River. So again, any land that drains water into a specific body of water. Why do we care? It's a great way for us to understand how water moves, and especially if we have stormwater runoff or impermeable surfaces, things associated with more urban areas, or maybe agricultural runoff. If we understand the nature of our watershed and how the water moves, we can better mitigate the effects of some of this pollution. All right, so again, let's hear somebody else describe the same thing.
What is a watershed? Is it a shed that holds water? No. Try again. A watershed is all of the land that drains into the same location or body of water. People tend to think only of water bodies, such as rivers, lakes, and wetlands, as being part of their watershed. However, any land, whether it is park, farm, forest, school parking lot, and even the soil we build our homes on, is also included. Think of a watershed as a funnel, collecting all the water within a specific area and draining into the nearest body of water. Drop by drop, water is channeled into soil, groundwater, creeks and streams, making its way to larger rivers and eventually the ocean. Everyone in the world lives in a watershed. Watersheds know no political borders, whether local, national, or international. Our environment, our economy, and our society all depend on a healthy watershed.
And what's below that watershed? Our soils. All right, so our last topic is El Nino and La Nina. This is Unit 4, Topic 6. So by the end of this section, you should be able to describe the environmental changes and effects that result from El Nino and La Nina events. So to get there, we'll describe what's happening during those events, and then describe the effects. What's the environmental results of those two events? So you'll notice I've used the word event, and that's important because it's a departure from the normal. And what is the normal? Well, this was what was described by Ms. Fassler the other day. She did a great job of talking about how the difference in solar insolation with latitude kind of heats the Earth unequally, and so that we have a unique distribution of heat in the ocean and in the atmosphere. And because they're unequal, we get a flow of heat. So air and water both will help circulate heat around our planet. And because of that, we get this typical pattern. These patterns, these conveyor belts of ocean that move around planet. So before we study El Nino and La Nina, we need to describe what normal is. What is the normal normal pattern going on with these winds and waves or water currents. So this in particular, this event, El Nino and La Nina, happened in the Pacific Ocean, in the tropical waters of the Pacific Ocean. So here's what the normal pattern is. The normal pattern is the winds and Coriolis effect cause equatorial, so on the equator, equatorial surface waters, not deep waters, equatorial surface waters in the Pacific Ocean to flow from east to west. So here's a little diagram. So here is North America, Central America, South America, and here is Australia, Southeast Asia. And so what typically happens is we have this weather pattern in which the wind moves this way and pushes warm water to the other side of the Pacific Ocean. And so what happens is we end up having this big accumulation of warm water in this part, in the western part of the Pacific Ocean. So let's diagram this out a little bit more, make it more clear. So the normal pattern, we get these winds blowing from east to west, and those blowing winds move the surface waters of the ocean, which is obviously warmer than below. So now we have this big accumulation of warm water over here, and that's obviously going to affect the amount of evaporation and rain that will happen in this area. But it also affects what's going on below the water as well. So just like in a bathtub or a pool, if water hits the side, it's going to have to be forced down, and that's going to push this colder, deeper, nutrient-rich water up, and that's called an upwelling. So in the eastern part of the Pacific Ocean, we now have colder, deeper, rich water kind of coming up to the surface because of this movement of the warmer current in the opposite direction, like a little circulation here. Why is that upwelling important? Because all those nutrients make the waters more productive. So we have lots of fish populations increasing, and obviously that's going to be a huge boom for fishing industries off the coast of South America, Central America, places like that. All right, so that's what's normal. That's called the neutral condition. What we're going to look at today is what happens if that gets accelerated. So it still moves in the same direction, just a lot stronger. That's La Nina. But sometimes it can actually go the opposite direction, and the winds blow in the opposite direction. That's called an El Nino. So again, neutral, very accelerated neutral, opposite of neutral. But let's go back to neutral. Let's have someone explain that again. Now I picked clips from Australia today because I think it's useful for us to understand the effects of El Nino and La Nina on a location other than North America. So when you think about the effects of El Nino and La Nina in this situation, we're talking about Australia.
This climate. Well, during the neutral phase, steady trade winds blow across the tropical Pacific from the east to west. These winds pile up warm water in the western Pacific. In contrast, water temperatures to the east are lower, as the trade winds cause cool water to be drawn up from the deep. The temperature difference across the tropical Pacific Ocean causes air to rise to Australia's north and descend near South America. This creates a huge connected cycle called the Walker circulation. We consider neutral.
So that's the neutral condition. That's what's happening normally. But every 3 to 7 years, we have an El Nino event. So this is a natural disruption from the normal pattern in which the currents move in the opposite direction from west to east. And you'll notice what happens is we get this buildup of warm water over here where it used to be over here. So the opposite is going on. The wind is moving in this direction, and that's pushing the surface waters in this direction, and it's really lowering, if not stopping, that upwelling feature. So we have warmer sea surface temperatures in central and eastern tropical Pacific Ocean. That upwelling is affected and can clearly affect fisheries. And that can last weeks or even years. What else will it do? It's going to change weather patterns. So it's going to dramatically alter what typically was happening, because no longer do we have this big bulk of warm water over here. It's now shifted on the other side of the Pacific Ocean. So we might have wetter conditions in the southeastern part of the United States, or we may have drier conditions, drought conditions in southern Africa, Australia, or Southeast Asia. And if they're dramatic enough, they could actually affect crop production and result in some food insecurity for some individuals. All right, so let's take a look at the video explanation of El Nino. So this, remember, is reversing what normally happens.
On the other end of the scale, we have El Nino, which is almost the direct opposite of La Nina. During El Nino, the trade winds actually weaken or reverse, allowing warmer waters to drift back towards the east. The change in the ocean temperature patterns mean the Walker circulation breaks down, resulting in even weaker trade winds and even more warming in the east. Once this feedback starts, El Nino has set in. With the warm water shifting east, the evaporation, cloud, and rain follows, shifting away from Australia. That means a greater risk of drought for northern and eastern Australia, higher temperatures and more heat waves, clearer nights and a longer frost season, and fewer tropical cyclones.
All right, so that's El Nino. Now let's go La Nina. So La Nina is the normal condition, this normal pattern of the trade winds moving westerly. It's just increased. It's stronger. So it's an exaggerated version of normal. So much stronger winds blowing westward, and the result is we have much colder water in the eastern part of the Pacific Ocean. So here is a description of La Nina.
When we move into a La Nina, it's a bit like the neutral phase has gone into overdrive. The trade winds blow harder, expanding the warm pool on the Australian side of the tropical Pacific and cooling the oceans towards South America. This increases the east to west temperature difference and makes the Walker circulation even stronger, and the trade winds blow even harder again. This is called a feedback loop, and once it starts, we're locked into a La Nina until at least the following autumn. With the higher ocean temperatures, we get greater evaporation, more cloud, and more rain in the western Pacific. For Australia, this means a higher risk of widespread flooding, lower daytime temperatures, and more tropical cyclones.
So we've got a situation where the simple change in the directionality and the strength of these trade winds can really affect what's going on not only the ocean and the atmosphere above the ocean, but on either of those sides of the Pacific Ocean. So you'll notice that this is an oscillation. So it's something that can swing back from La Nina back to normal, back to El Nino. But this oscillation is why it's typically called ENSO, El Nino Southern Oscillation, because it does oscillate between the different conditions. Why is it called El Nino? Is because fishermen in Peru saw this dramatic decrease in their fish catch, and it happened to happen around Christmas time. So they call it El Nino for rice traps. All right, so that's our stuff for today. Let's do a quick check for understanding. So this question says, during an El Nino Southern Oscillation event, which of the following best describes conditions in the eastern part of the tropical Pacific Ocean near Peru or Ecuador? So El Nino. So hopefully you pick D. So we would have high sea surface temperature and high rainfall on the eastern part of the Pacific Ocean. This is taking us to soil. So let's read what this question says. It says a military training site is interested in determining the effect of training activities, primarily foot traffic, on the soil. So they established 4 test sites. In site number 1, they permanently sectioned it off. No one could walk through it, so no foot traffic. In site number 2, they sectioned it off 5 days out of the week. So 2 days out of the week, people could walk on it, had light traffic. Site 3, they sectioned it off 3 days a week. So 4 days of the week, people could walk on it, so had medium traffic. And in site 4, they didn't ban walking at all, high foot traffic. So for each of these sites, they measured the leaf litter, permeability, and erosion. These tests were done twice, once at the beginning and once again after the 6-month experiment was over. What type of data trends do you think you will see in the table? So take a second and look at the table and see if you can identify a trend that might show up. So in site number 1, we may see the leaf litter actually increase because no one's walking around and the amount of leaf litter is building up. And we might see the erosion actually go down a little bit because no one's walking on it. Whereas in the other sites, we should see obviously a big drastic decrease in leaf litter. The permeability is probably going to become lower and the erosion is going to get higher because we're walking over all those plants and trampling them and the roots are dying off. So just an example of how these soil tests can be used in an experiment. So the next one we're going to look at is from the 2016 exam. This is question number 4. It says soil is a complex mixture of living organisms and organic material along with minerals and other abiotic components. Soils help sustain life and support ecosystem functions. A. Describe how 2 climate factors affect the rate of soil formation. So let's look at that one first. So take 30 seconds or so and think in your head, how would you describe how 2 climate factors affect the rate of soil formation? All right, let's look at somebody else's answer. Let's look at a student sample. So it says one climate factor is temperature. With soil formation, a cold temp could slow down the process of breaking down organic compounds to make soil. Boom, there's a point. Absolutely. Temperature is going to affect decomposition rates, for example. Then they say precipitation is another factor with soil because it keeps the soil moist and rich with nutrients when it rains often. No points there because they did not connect how this climate factor affected soil formation. So what we were looking for with temperature, or with precipitation, I'm sorry, it says if there was a high precipitation, that might increase biological activity or weathering, but if it was really, really low, maybe it would do the opposite. And another option with high is you could say if there's a lot of rain, you'll get runoff. So therefore it would decrease the rate of soil formation. Because this is a describe, you have to show how the abiotic climate factor that you talked about will affect the formation of soil. Note at the very bottom, no point earned for merely identifying a climate factor. The second one says, as soils form, distinct layers known as horizons develop over time. One of these is the A horizon. So identify one specific biotic component and one specific abiotic component. So let's look at someone's response for A or BI, identifying biotic component. They said biotic component of A horizon is that several earth-dwelling creatures like worms and bugs dig into this area to call it home. Boom, there's a point. Worms. For abiotic, they said an abiotic factor is the soil formation. This area has a good combination of silt, sand, and clay that allow water to easily travel through it. Boom, point for silt. Point of caution. Notice the question says identify one. This person actually identified many. Worms and bugs, sand, silt, and clay. So if a question asks you to identify or describe a certain number of things, be sure you only give one because these ones come afterward will not be graded. And there's the official answers there. So biotic is all of the organisms that live there, and abiotic is sand, silt, clay, air, water, pH, all that stuff. All right, so where did we go today? We talked about soil formation and erosion. We talked about how the soils are different and how those differences can result in changes in their chemical, physical properties. Then we described what a watershed is. And then finally, we looked at the El Nino and La Nina events. And again, remember that these soil tests are a really nice place to practice your ability to use them in scientific experiments. So your homework for tonight is going to be an FRQ again. So remember your task verbs. And this is going to be about you working with some soil samples. And Ms. Fassler will go over A, B, C, and D with you next time. So just a quick reminder about electronic connectivity here. So we know that not all students have access to the internet or device. We're working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity or know someone who does, you can reach us directly to let us know by this Friday. So this Friday is the cutoff time for the College Board to respond to these requests. So be sure you do that for them. All right, have a wonderful day. I'm so glad to have you back with me here, and I'll see you next time. Bye.
Hi, everybody. Welcome back to our AP Environmental Science virtual classroom. Thanks for joining me today. My name is Ms. Fassler, and I teach APES at Marshfield High School in Marshfield, Wisconsin. So guess what? We're going to start with a warm-up and go over the question that you looked at yesterday with Dr. Sowell. When you finished up Unit 4, you got this great question on soil testing, which really nice example of some experimental design. So let's see how you did. The first prompt asked you to identify and describe. We'll dig into how the rubric addresses that in a minute. You needed to look at both one chemical soil test and one physical test, and then relate those to how you would present some sustainable agriculture recommendations to the farmer that brought that soil sample into you. You are working at your dream summer job as a soil tester for a cooperative extension service. So that's where people are going to bring their soil samples. You're going to give them feedback and make some recommendations. So let's take a look at the chemical tests. I think that most students went with sort of those classic or chemical tests we often do on a soil sample pH, and then the amount of nitrogen, phosphorus, or potassium. Note that even though I had to describe in order to get the 1 point for that, the rubric indicates that the name, if I say I'm going to test for nitrogen, that really is kind of a description. There's not much else I have to say about that. In terms of the physical tests, there's a lot of options there. I think the most common was probably a student saying, I want to test the soil texture in some way. And notice there's a couple of different ways you could have described the soil texture, that term, rather than using soil texture. And a description of the test itself would be looking for the relative amounts of sand, silt, or clay. Other common tests, the water holding capacity, the permeability. You can see there's a pretty broad list there. Excuse me. The third point here then was what kind of recommendations would you make based on these results? And you can see things like, oh, if my soil was low in nitrogen, one of those tests I did, perhaps my recommendation is to plant a legume or a nitrogen fixer. Maybe I would want to add either sulfur or lime the soil depending on my pH to neutralize it. And you're actually going to look at sustainable agriculture practices tomorrow, so these will make a lot more sense to you then. The next one was looking at explaining one advantage and one disadvantage of an inorganic commercial fertilizer. Let's just make sure we're clear what they mean by that. And although the question doesn't ask me to compare it to an organic fertilizer, let's just make sure you're clear on what we mean there. That inorganic commercial fertilizer it does not have decaying organic matter or humus in it. I purchased it. It was manufactured in a chemical manufacturing plant. I go to a store and I purchase that, and it's a salt that I apply to my field or my lawn if I'm going to fertilize my lawn. And then when I water that or when it rains, that salt goes into solution. And so many of the advantages of that relate to understanding what exactly an inorganic commercial fertilizer is. So it's pretty easy to just go into a store and buy that big bag of fertilizer and transport it, store it, and then apply it to my field when I need it. And once that goes into solution, those nutrients are readily available. That salt goes into aqueous solution, and now plants can take that up when they take up water. Disadvantages of that have to do with the fact, I think probably one direction a lot of students went was that runoff and that issue of eutrophication or over nutrient enrichment of surface waters. You could have talked about the fact that it doesn't add anything to increase the texture or bulk of the soil structure. And again, if I could compare that, it makes more sense if I wanted to add an organic fertilizer, that would be compost or animal manure. When I work that in, it's going to change the structure of my soil. It's going to increase the water holding capacity, prevent erosion or runoff. Adding this inorganic salt that goes into solution doesn't have any of those advantages. There's a lot of harm with actually harming the plant, a lot of potential to over fertilize and put the wrong concentration down. And then I just want to mention this one, even though greenhouse gases aren't assessed on our exam, the nitrogen cycle and air pollution are. So remember that in the microbial, when I put that fertilizer on my field, the soil microbes can convert that form of nitrogen into nitrous oxide that can then enter the atmosphere where it is a potent greenhouse gas. Letter C was to describe 2 soil conservation practices to decrease erosion. Again, you're going to really dig into this a little bit more tomorrow, so I'm just going to give you a second to look at that, and you'll go back and review that more in sustainable agriculture tomorrow. And then letter D was 3 points for looking at, actually 4 points. We have to list a biome that's rich in humus. We have to describe how that humus originated and provide 2 ways that humus improves conditions for plant growth. So notice that the biomes that were accepted were not just forest, and we're going to point that out in a minute. I could say a deciduous forest or a temperate forest. I could say a temperate rainforest, or I could say a grassland, a temperate grassland like a prairie, and all these different terms we have for prairie. prairies. How that humus originated was really just the decomposition and buildup of organic matter. In a deciduous forest, we use that term leaf litter, I think, when we look at the word invasion. So all of that leaf litter and plant and animal material decompose, and those nutrients are then released. How it improves soil condition, it increases the fertility. And this is where I was going with the previous question. This humus is like that compost that I might add on purpose to increase the nutrient concentration in my soil. And the humus gives me all those advantages of holding water and retaining water and preventing erosion. The other thing I wanted to point out here was that tropical rainforest is not an acceptable biome. We're going to explain that in a little bit when we look at slash and burn agriculture and tropical rainforest. So if you're questioning why not a tropical rainforest, just hold on to that thought. So where are we going today? Well, we finished Unit 5. Unit 4. And today we're moving into Unit 5. And guess what? We're going to focus on describing or explaining an environmental concept, process, or model. And just like in that last homework FRQ, you really dug into the experimental design. A lot of what we do in Unit 5 lends itself to proposing and justifying an environmental problem. We're still not forgetting about this. We have 3 units left to review, so we'll have plenty of time to go over both of those specific portions unique to each of the 2 questions. I just wanted to take a minute and mention a little bit about organizing yourself for the national exam. It's still 3 weeks away, but as you're watching the videos, I want to make sure you know that you can use notes on the exam. While you're sitting at home, you can use any notes or resources that you've generated, and the College Board has put together a really great document that gives you some tips for how to take an open notebook test. We certainly don't want you to have this impression that it's going to be a piece of cake because it's open notes. Oftentimes, students get sort of this false sense of security. So as you're watching the videos and you're going through this review process, keep that end game in mind. We are taking a 2-question, 3-response exam. It'd be a little bit different if we were taking multiple choice questions on the exam. How I organize my notes and what I include in them might be a little bit different. I certainly need facts and details to put some meat on my description and explanations, but keep in mind how you're going to be assessed on the content and how you're going to organize your notes as you're going through the lectures, that you really want to start visualizing what that test day is going to look like when you sit down with those notes in front of you and how to make the most out of that as well as manage your time. So we're moving into Unit 5 on land and water use. This unit explores human activities that disrupt ecosystems. This is the part of the KH curriculum that can tend to get a little depressing to students because there's a lot of ways that we can negatively disrupt ecosystems. And that's why we really try to spend a lot of time focusing on the second part of this learning objective in providing strategies to mitigate or reduce or solutions to solve some of the impacts that humans are having. In our discussion today, in the first of 3 lessons of Unit 5, there's a lot of learning targets in this unit, so we're going to spread it out over the next 3 days. Today, we're really going to focus on how will our systems and processes provide for future generations. And in order to do that, we're going to shift the order a little bit, and we're going to kick off with learning target number 12, an introduction to sustainability. We'll go into tragedy of the commons, and just to start to kind of introduce how agriculture systems might positively or negatively impact the environment, how human activities through agriculture might impact the environment. And the big ideas that we're going to focus on are how the species interact with their environment, humans interacting with the natural world, and the way we use resources, and obviously this big idea on sustainability and the challenges that we face in ensuring that we are leaving resources for future generations. So the term sustainability itself, let's start with kind of a review of what we mean by that and sustainable resource use. If you think about it, it's inevitable that we as humans are going to alter natural ecosystems as we locate, extract, and process different resources, whether those are energy resources, different mineral resources, renewable resources. We have some impact. Our activities are going to have an impact. And in fact, we scientists have now coined the term Anthropocene to describe the current geologic epoch that we're in, where it's really human activities that are being the dominant influence on the environment and climate. Versus if you look at what we've done over the last week or 2, we looked at natural selection and how over a period of time organisms can adapt to a rapidly changing environment. And we just finished up that Unit 4 on geologic processes. So we know how our Earth should function when things are working well. We know that there are changes and impacts, natural impacts all the time. But I guess the idea of sustainability to me really implies this balance. And the term really kind of started first being used around Earth Day, and how coincidental we are celebrating 50 years of Earth Day tomorrow. Everybody wear your tie-dye. And so it's like a balancing act. We have to extract resources. We have to grow food. We have to have energy. We have to have houses and other things. But how do we do that in such a way that we ensure that future generations are going to have access to those same life-supporting processes that our planet naturally does to supply us with these natural resources? So 50 years of Earth Day. Earth Day was kind of the brainchild of Wisconsin U.S. Senator Gaylord Nelson, and the University of Wisconsin currently has the Nelson Study for Environmental Science, a fabulous institute that honors the work that he did. So as we start digging into sustainability and sustainable resource use, I'm going to kind of focus a little bit on these environmental indicators. Think of it, if you go to the doctor for a physical, the very couple of first simple easy things they do, they take your temperature, your pulse, and your blood pressure. These environmental indicators are the pulse and the temperature and the blood pressure of our planet. They're these key indicators of kind of how well we're doing on using resources in a sustainable way. So let's just look at a couple of those to get us thinking about the idea of sustainability. Certainly one of the key environmental indicators is population growth. We simply have a lot of people that are going to need access to life-supporting earth processes and earth resources and all these ecosystem services that provide for human life on our planet. And so we obviously face challenges with sustainability when we have more and more people wanting to access the available resources. One reason that scientists have coined the term Anthropocene, and this really kind of drives home that point, is the drastic increase in extinctions across all different taxonomic groups relative to the typical background or normal rate of species extinction. This is a high blood pressure that our planet is calling out to us that there's something wrong. Certainly, we cannot ignore the indicator of increasing levels of carbon dioxide concentrations at rates and up to levels that we have not seen throughout 800,000 years of geologic climate, recreating of geologic climate, and all of the direct and indirect implications of increasing CO2 and a warmer planet. Probably one of the key indicators of a warming planet is one of the first things climate scientists alerted us to in the 1970s when they first started publishing papers on the what they predicted were going to be some of the consequences of increasing concentration of greenhouse gases in the atmosphere, and that is both the number of severe weather events and the severity, the intensity of those severe weather events. And if you kind of picture a little bit of a trend line through here, you can see that we are drastically increasing the cost to our future generations. We are leaving them with an economic system that may not be able to absorb the cost of all these drastic changes that we're causing. So again, a little bit doom and gloom, kind of to lay out as we review those core ideas of sustainability. And that leads us directly into a review of this concept of tragedy of the commons. You may remember talking about this. You may have done a little fishing activity on it. It's this idea that was first proposed by Garrett Hardin that individuals will often use shared resources with their own self-interest in mind, not keeping in mind the common good. Hardin's original work focused on overgrazing of animals on a commons. And by that we mean a resource that nobody owns privately, but is accessible to the common, to the general population, if you will. And so he observed the overgrazing of animals on common grassland or rangeland. Very easy to make that connection to overfishing of the world's oceans, a topic that we dig into in one of our next 2 lessons in Unit 5. The oceans is a commons, and each individual fishing company says, I'm just taking a little bit, my limited little catch, and we start adding that up with the magnitude of everybody that's doing that. We realize that we are overfishing or using that resource in an unsustainable way. The atmosphere is another good example of a commons, and the amount of photochemical smog and particulates that will endanger the health of future generations. And deforestation, primarily in tropical rainforests, another example of a commons, and we'll dig into this a little bit later in today's lesson. Well, let's take a look then at if we've made this connection between, we want to make sure that we use resources at a level that we leave some for future generations, and we know that we as a species tend to sort of think about our own personal needs being fulfilled first without a broader look at the good of the entire population. That's where this idea of sustainable yield comes in, and it's driving us towards some of these solutions or a positive way to look at it. How can we manage renewable resources? Non-renewable resources, I mean, oil is going to be gone someday. We can spread out how long that oil lasts by reducing the amount of it we withdraw, but there's a finite amount of oil on the planet. So when we look at renewable resources, we like to look at them in terms of sustainable yield. We want to determine what's the maximum rate at which I can harvest that natural resource without depleting it. And a really good way of thinking about this is if I look at the carrying capacity of a population and how many, if I'm going to say, like, if you're hunter fish at all, the wildlife biologists each year will do a survey of a deer population, and they'll say, well, here's what our population is, and here's how many deer tags or licenses we need to distribute in order to ensure that we have enough of a stock of deer left that they can quickly rebound and get back up to carrying capacity. So we can really apply this idea of sustainable yield to any renewable resource. Are we using it at a rate that it is going to be able to replenish itself? And again, we're going to look at overfishing and deforestation in a lot of detail now that we've reviewed some of the basic ideas in this first lesson. So let's take a step back and see if we can apply that by looking at a quantitative data set and looking at groundwater withdrawal. Groundwater is another example of a commons. This graph simply shows me from the year 1970 to 2010 the amount of water withdrawal in cubic kilometers per year. It's a volume unit. And I can see that overall we're withdrawing more water. Let's talk a little bit about some of the details on the graph, and then we'll look at groundwater itself. So they could ask me a simple question to just interpret the graph. Which sector uses the greatest amount of water? You may have known that without looking at the graph, but it's agriculture. And the source of that water, where most of the water for irrigation comes from, is groundwater. Not all of it, but that's where a large source of it's from. You're going to dig into irrigation techniques, I think, tomorrow a little bit more. So what I want to spend a minute on is just kind of talking about groundwater as an example of a commons. You may, I'll go to the color coding here that you probably can't see in a minute, but you may remember talking about the Ogallala Aquifer. It's a big geologic source of water that we tap, groundwater that we tap to grow agricultural crops. And there are other aquifers in other parts of the world that are tapped for growing agricultural crops as well. The majority of the water that fuels the growth of crops in the breadbasket of the United States, where we grow a lot of corn and wheat and soybeans, pretty much all of that comes from the pumping water up from the Ogallala Aquifer. And remember, when we talk about that aquifer, we talk about it as a geologic source of water. The geologic processes that accumulated all that water as like thousands, over the last couple of thousands of years, water percolated down through that soil and saturated or filled the rock below and layers of porous soil. So we now have this big reservoir, this big storage area of water that we can tap. But according to this graph, we're not using that water sustainably. We are withdrawing water at a rate. We are pumping it out faster than like snow melt from the Rockies can run down and trickle in and recharge that aquifer or replace what we withdrew, because the rate of withdrawal exceeds the rate of recharge. And these red and orange areas are showing the areas where the aquifer has been very substantially depleted. There is no way that a couple generations from now, there's going to be water left in the Ogallala Aquifer to farm the way that we're currently farming, using the amount of water that we're currently using it. We are using it at an unsustainable rate, which means we are going to prevent future generations from having access to water, potentially having access to water to grow crops. We'll come up with some solutions for that. So the idea of sustainable use applies to the management of renewable resources. So we've kind of started looking at this idea of agriculture. I'm going to introduce some of the background information on agriculture, starting with slash and burn, looking at kind of an ancient technique of agriculture that people would use individually on a small scale. Clearing a plot of land to grow enough food for subsistence farming is really the technique that this is used for. So if we were going to describe what slash and burn agriculture is, it's a method of growing food in which we clear often forested land and we burn that vegetation. We slash it, we cut it, and we burn it. Why do we burn it? Well, all the nutrients are stored in the trees. So that ash contains all the nutrients, and I have this rich layer of nutrients on the top of my soil so that I can grow a crop. It happens mostly in developing countries, rainforested areas of Africa, northern South America, parts of Asia. This map in particular indicates areas that have been slashed and burned for palm oil plantations. That would be an example of a cash crop, or why slash and burn agriculture is posing such an unsustainable threat. It might be to grow cash crops, it might be to clear pasture land for grazing livestock, or it could be just an individual farmer needing to clear land in the rainforest to grow food for their own family. So the explanation why it's an unsustainable practice, this is where we're going to go back to that tropical rainforest from your soil FRQ that you did for homework. Tropical rainforests do not have a lot of organic matter in their soil. They are very nutrient poor soils. And it seems sort of contradictory. We think, well, look at all the stuff growing in the tropical rainforest. There's got to be nutrients in the soil. But the thing is, tropical rainforests don't ever have a dormant season. They're at the equator, they're getting all that sunlight, lots of precipitation, and they're just growing all the time. In a temperate deciduous forest, like where I live, all that leaf litter falls in the winter, and then nothing's actively growing a lot in the winter. So all that leaf litter gets to slowly decay, and that organic matter builds up over time. That just doesn't happen in a tropical rainforest. The minute something dies, it's decomposed, plants immediately take that up, and we kind of say that all the nutrients are in the trees themselves. That's why when I burn them, the ash has all the nutrients, but this is unsustainable because pretty soon there isn't going to be any nutrients left in that soil. That ash only worked for a couple of years, and now I have a barren piece of land that won't support the growth of anything. We are chopping trees at a rate faster than they can be replenished. So let's take a look at a short video clip that shows you a little bit about what slash and burn agriculture looks like, but we're also going to hear from a farmer that's just trying to do subsistence farming and their point of view, looking at this rainforest and slash and burn in terms of tragedy of the commons.
And we turn now to a story about changing age-old farming practices in the tropics. It's part of the Economist Film Project, Newshour collaboration with The Economist magazine. Together, we showcase independently produced documentaries that take us places we don't ordinarily go. Here's an excerpt from Up in Smoke by filmmaker Adam Wakely. He followed ecologist Michael Hans as he introduced Honduran farmers to the Inga tree, the solution to the problems caused by so-called slash and burn agriculture. You start the fire there. Okay, this is where we burn. Weeds and trunks of it. You can't plant amongst all of that. So we just burn it all. I know this destroys the soil. Fertility disappears. I know this. But there's no other way to eat. Do you understand?
So what we saw there was kind of a classic example of tragedy of the commons. Each individual farmer saying, I have to eat, I have to clear this land to plant a crop. And as the film continues, and tomorrow we'll talk about the solution part of it, we'll come back and look at what solution they're presenting to those 100 farmers. But he said each year we just go up and clear another couple hectares and we keep spreading out. And then like the next year, even 2 years later, they clear another patch of land. And you get the idea that everybody's doing that. The magnitude of that means that we're clearing forests at an unsustainable rate. So let's switch gears a little bit and go from that agriculture practice that's used just to feed a small number of people to the Green Revolution. These remarkable breakthroughs that happened in scientific advancements in the 1950s and 60s. The Green Revolution was really spearheaded by this American agronomist, Norman Borlaug. And what he did was the process of selective breeding. And I'm going to take just a minute to explain that so that next when we talk about genetic modification, the difference makes sense to you. Selective breeding is artificial selection. We learn about natural selection where nature decides through natural changes in the environment, what traits are going to be most advantageous. Well, a plant breeder, an agronomist like Borlaug, selected artificially which traits he thought would create the best wheat plant. And he developed this dwarf variety of wheat plant. You may remember reading about that when you studied the Green Revolution in your class. So instead of having this normal wheat plant that had a lot of energy was going into making the stalk and things like that, he developed this dwarf variety where all of the edible energy went into those kernels. And then the result was just a lot more grain to feed a lot more people. And the results were dramatic. Throughout the 1960s up through the 1990s, similar varieties of rice were developed. Borlaug really focused on the wheat, but the promise and benefits of the Green Revolution were most seen throughout Asia. And in fact, the population, that's because that's where a lot of population increases were happening. Even though the population increased over that period dramatically in Asia, we saw death rates fall and the amount of actual food people were consuming per person go up. I believe it was 1970 that Borlaug won the Nobel Peace Prize, and he's credited with saving 1 billion lives through the development of these hybrid type of plants. So the Green Revolution was phenomenal in developing for certain parts of the world that were dealing with rapidly growing populations in saving them and giving them enough food to eat. And that sort of led in the developed world. At the same time, we were developing these techniques of industrial agriculture. So I'm just going to kind of introduce and review what we mean by industrial agriculture, and again, dig into the real specifics of that over the next lesson or two. So if I were going to describe or list the characteristics of an industrial agriculture practice, I would have to talk about the scale of it. It's very large scale. It could be, I have a field I'm harvesting anywhere from thousands to 10,000 acres, and it's a monoculture. That implies one variety of crop, often corn or wheat or soy. And in order to understand the implications of a monoculture, think of the Irish potato famine and what happens when we rely on only one type of crop. And the loss of those ancestral varieties of things like wheat and rice and corn are going to be very significant. We'll come back to that in a minute when we look at genetic modification. The next characteristic we have is that it is mechanized. We've really increased output. We've increased the efficiency. I can produce a lot more grain per acre, per unit of land, but that comes at the cost of increased use of fossil fuels. The tilling techniques that are required for many industrial agriculture processes dig deep into the soil. They can damage the soil structure, and more significantly, they're altering that. They're digging through that soil and releasing a lot of carbon. That soil should normally be sequestering vast amounts of carbon, but these tilling techniques often release a lot of that. And back to this idea of fertilizers, large inputs of nitrogen and phosphorus, because they are limiting factors in a terrestrial ecosystem. There is no way that we could ever have kept pace, that food production could have ever kept pace with human population if we didn't supplement the nutrients in the soil in some way in a large-scale agriculture practice. And remember, those nitrates and phosphates, N and P, that are plant food, run off and serve as plant food for algal growth. And we get this process of nutrient enrichment where when those algal plants die, the decomposers deplete the oxygen, and we have these huge dead zones in the Gulf of Mexico. So all of these ways that we just described industrial agriculture are also pointing to signs, those vital signs or environmental indicators that we're doing this at an unsustainable rate. We're using fertilizer, fossil fuels, depleting water resources in such a way that we're jeopardizing the potential for future generations to produce food. Well, scientists often come to the rescue with some solution like that. And one of the things, because we feel that the techniques that we've been using for agriculture over the last couple of decades that has shown us those drastic increases in yield, amazing increases in yield, we believe we are maxing out our capability of soil to keep increasing the amount of food we can produce per acre. So next we're turning to genetically modified organisms. Remember, that is not what Borlaug did with the agronomist, where he just took the traits of, he looked at the genetics of plants and said, I'm going to take this plant with these traits and this plant with these traits and breed them together to get a new variety that has the best traits. When I genetically modify an organism, I, in a laboratory, create a seed that has, I've altered the genetic makeup of that existing plant. Often that implies inserting a gene from, it could be a completely unrelated species. It could be inserting an animal gene into a plant. Well, why would scientists want to do this? Most of the benefits, and remember early on we said that human impacts have both positive and negative implications. Some of the positives that have come out of genetically modifying seeds is that I can create a seed that will often allow it to overcome some of the other environmental problems we created. So we have a warmer climate. So I might want to genetically modify a seed that can grow in a warmer climate or a warmer soil. Or we know that there have been changes in precipitation patterns as a result of climate change. Maybe the area where I typically grow my corn isn't getting as much rain, or it's getting a lot more rain. So I might want to modify its ability in terms of its drought resistance, or maybe more tolerant to salt as soil is becoming salinated. I might also want to modify it to take repeated applications of an herbicide. You may have talked about Roundup Ready in your classroom when you talked about this. So the benefit is that if my seed is genetically modified, the minute my soybean plant emerges, normally I couldn't spray my herbicide because the herbicide couldn't tell the difference between the weed and my soybean plant. I don't want the herbicide to kill my soybean plant, but a Roundup Ready seed will not be killed by spraying that herbicide. So I can continually spray herbicide. The benefit of that is that I increase yield. I have less cross crop loss to weeds. And it could be genetically modified so that is a built-in pesticide. You may have talked to BT corn. They genetically modify seed so that it has its own natural pesticide, so that a corn borer insect, for example, may not eat my crop. It would die if it ate it because the insecticide or pesticide is already in there, and I'm not spraying it. That would be the benefit of that, is that it's only in the plant, and I don't have the negative consequences of spraying that broad-range pesticide. Well, some of the concerns about that, we've created this monoculture. We're losing ancestral varieties of different crops like wheat. And if I want to ultimately create a genetically modified wheat crop, wheat seed that is going to be drought tolerant, I have to have a lot of different kinds of wheat plants to seek out that gene that naturally exists in some wheat plant somewhere and take that gene and insert it into my new wheat plant that I want to genetically modify. So this seems a little confusing at first. How can taking repeated applications of an herbicide be good and bad? Well, it's good in terms of my crop yield. It's bad because I'm spraying a lot of herbicide. And some of those herbicides are persistent organic pollutants that can cause both environmental and human health effects. Built-in pesticide. It's good that I can build that pesticide right into my seed and the farmer doesn't have to spray, but anything that eats that plant could now be affected by that toxin and it could die as well. It might not just be targeting that corn borer insect that I want to kill. There are questions about human consumption of genetically modified foods. There is no current research that shows any direct link between human health problems and eating a food that's been genetically modified. There are certainly environmental implications like loss of natural biodiversity, and many people may have a moral or ethical or religious problem with the genetic modification of an existing species. So let's do a quick check for understanding a couple multiple choice questions on what we just covered. Which of the following describes a fundamental characteristic of the green revolution in food resources? Question or choice A at first may have looked like it was pretty good, but remember it implies developing a new strain of crop, primarily wheat and rice, that have very high yields. Which of the following statements about genetic diversity is true? And the answer is genetic resistance to pests and diseases can be increased by crossing crop plants with ancestral varieties. And then we have a question here where we're going to look at a graph. This is about glyphosates. They're one of the types of herbicides or weed killers that we've talked about. And they're herbicides often incorporated into a GM crop to kill weeds without harming the crop themselves. So this is what we just talked about. There's a lot going on the graph here. So let's, like we've learned with that I-square technique, break down what's going on. Obviously, my x-axis is time from when we first started using glyphosates up until 2010. But I've got two different axes, two different scales on my y-axis. I have the amount of glyphosate applied in tons, and then my other axis, and that's the solid line. And the other axis is confirmed number of glyphosate-resistant weed species. Oh, that's something we haven't talked about yet. We know that plants and animals can develop a resistance. So that's this dotted line right here. And you notice, again, before I even read the question, I want to just take that couple of seconds and do an initial interpretation and make sense of this. So I can see that the use of glyphosate herbicides has increased dramatically. Look at the slope of that line. And I also see that after a little bit of lag time, it appears as if the number of glyphosate-resistant weeds increased at a mirror, it's like a mirror image, increased at the same rate after that little bit of lag time. So now let's take a look at the multiple choice question. Which of the following statements best explains the relationship shown on the graph? And letter C is the correct answer. The use of glyphosates has selected for herbicide resistance in weed populations. Now remember, I'm not going to go over a lot of multiple choice taking strategies here, but we did just talk a lot about a lot of environmental concepts and processes. Genetically modified organisms could be used as a solution. You could maybe be asked to talk about some of the pros and cons of that. And certainly one of the disadvantages in this specific instance of genetically modified seeds to take more application of these glyphosate weed killers is that eventually that crop is going to become resistant to that. All right, let's do a little debrief and summary. Go back to that original question that we looked at the beginning. How will Earth systems and processes provide for future generations? So we had those learning targets about what is sustainability and the idea of sustainable yield. We looked at tragedy of the commons and related that to sustainable resource use. We reviewed the Green Revolution, what the Green Revolution was, and how it was able to increase yields, but some of the drawbacks of that. And finally, we just introduced the idea of some different kinds of agriculture practices. And tomorrow, you're going to, as I said, you're going to dig into those in a little bit more detail. So I'm going to leave you with your homework. It's a little bit of a shorter assignment. There are 3 task verbs that you're using in this homework assignment tonight. Describe, I think it's an explain how, and identify. And again, before you do this, you may want to take a look at that note-taking skill because all these FRQs you're writing should be organized in your notes that you can use on the national exam. Let's do a quick preview of the test that your homework, the FRQ you're writing. Figure 1 shows the amount of sediment and runoff in disturbed areas, in areas where clearcutting has disturbed the vegetation in the riparian zone in a stream in Brazil. And again, I got kind of those 2 different y-axes. Why I got to tell you in a graph, I think it was on last year's exam, in grading that question, it was very clear that students didn't even realize that there were 2 different values represented on each side of that y-axis. So always do your I-square first. Sediment runoff and rainfall. So I've got sediment runoff represented by a bar graph in both non-vegetated and vegetated areas over this period of time measured in days. And then the line graph corresponds the amount of sediment runoff to the rainfall. In other words, what's the relationship between how much rain there is and how much runoff there is in both a disturbed and an undisturbed area. So a couple questions about the graph itself, and then we go into forests as a comments. Thanks for joining me today for the first of the 3 lessons in Unit 5. Have a fabulous Earth Day tomorrow, and I will see you on Thursday. See you guys.
Hello, everybody. Welcome to our review session for AP Environmental Science. My name is Dr. Sowell, and I teach APES down here in Jacksonville, Florida. So just before we get started, another quick reminder of our exam date and the 2 types of questions we have. First one being design and investigation, and second one is environmental problem and solution. So a quick note, I want to reiterate what Ms. Fassler said yesterday about a really useful page that talks about tips for success on open book, open note exams. Remember, this year's exam is going to ask you to apply information and to use information in contexts in terms of experiments or environmental problems and solutions. So taking notes on these videos that Ms. Fassler and I are making are great sources of information. But I would highly recommend looking at this URL, this page here, for some tips about how to best organize that kind of material. I also want to point out a new feature on AP Classroom that you may have heard from your teacher. If not, I want to point it out here. You now have access to more practice-free response questions. So you can go on there and select to do those yourself. They don't need to be assigned to you by your teacher, and you can practice them and check the rubric when you're all done. It's just another nice resource for you to practice some FRQs. All right, so first of all, happy Earth Day. Yay, happy birthday. I know Ms. Fassler said wear a Hawaiian or a tie-dye shirt, but I don't have one. So instead, we're going to have a little music interlude for happy Earth Day, so enjoy.
I see trees of green, red roses too. I see them bloom, for me and you. And I think to myself, what a wonderful world. I see skies of blue, clouds of white, bright, blessed days, dark, sacred nights. And I think to myself, what a wonderful world. colours of a rainbow, so pretty in the sky, are also on the faces of people going by. I see friends shaking hands, saying, how do you do? They're really saying, I love you. I hear babies cry. I watch them grow. They'll learn much more than I'll ever know. And I think to myself, what a wonderful world. Quite simply wonderful.
So happy Earth Day, everybody. I know you may be sequestered at home with quarantine or having your movements restricted, so you may not be able to go outside and enjoy Earth Day, the nature outside. But if you can, find a documentary, especially one narrated by David Attenborough, really great presenter. So let's warm up using the FRQ that Ms. Fassler gave you for homework last time about sediment runoff in undisturbed areas versus clear-cutting areas. And it gave you a graph with two y-axes. Remember, I always look for the axes and kind of dissect the graph before you jump right into it. So the first question said, identify the day of the study when the largest amount of sediment was present in runoff. So if we look for sediments, we know that this line here is rainfall, and that's using this y-axis over here. And then the sediment versus in the non-vegetated versus vegetated areas are the bars. So if I'm looking for the largest amount of runoff, here's the largest amount of runoff. It is on day 98. So day 98 was when we had the largest amount of sediment in the runoff. Please remember, if it says identify a day or identify a value or identify a number, it's not asking for a range. If you said somewhere between day 95 and day 100, that would not be acceptable. Identify means to give a particular value or number. Second one, describe the relationship between rainfall and sediment in the runoff. And clearly we can see that after big rain events, there was more sediment in the runoff. Based on the graph, explain how clearcutting has affected the water quality in nearby streams. So not only does clearcutting affect the amount of sediment in the runoff, but it can affect the quality of nearby streams. So you could increase the turbidity, so there's increased amount of runoff and sediment in the water. This could therefore increase the water temperature compared with the undisturbed areas as a result of a lack of vegetation at the mining location. So this is asking for an explanation, so much more than just a description. And this one says forests are often considered a commons or shared resource. They can often experience the tragedy of the commons. Describe one potential approach to reducing the occurrence of the tragedy of the commons in forests. So you could do things like legislation. You could pass a law that regulates how that resource is used. You could come up with a quota. You could only harvest so many trees, or perhaps there was a quota of trees that you had to replant. Another one is privatization, because we know a lot of times human beings will take care of their private property more than they will a shared resource like the commons. All right, so hopefully you did wonderfully on that. So let's jump into where we're going to go today. So today is all about more agricultural practices. So our goal is to talk about irrigation methods, so list some ways that we irrigate our crops, look at pest control methods, how do we deal with pests on our crops, meat production, how we produce meat, and then looking at two solutions for more sustainable agricultural practices, which are integrated pest management and a bunch of sustainable agricultural practices we'll list. We are also going to spend some time with science practice number 4, scientific experiments. Remember, that's the backbone of FRQ number 1. It's going to have some sort of work with experiments. So we're going to practice that twice today during this lesson, once in the middle of the lesson and once again for homework tonight for the FRQ. All right, so let's jump into it. So the first thing is the irrigation method. So after this little section, you should be able to describe the different types of irrigation and then the pros and the cons of each. And then that's kind of the description phase, and then be able to explain how different types of irrigations might have certain effects on the environment. So remember, we want to not just identify, yes, I know what drip irrigation is, but you need to be able to describe it, what are the characteristics of drip irrigation, and explain it. How might you use drip irrigation to mitigate some environmental effects? So first of all, we'll talk about the different methods. We'll talk about the pros and cons of each method. Then we're going to talk about two particular soil irrigation issues, soil salinization and waterlogging, and then we'll also mention briefly the Ogallala Aquifer. All right, so let's start with this basic statistic. The largest human use of fresh water is for irrigation, 70%. That's huge. That means all the fresh water we use on the planet, 70% of it we use to put on our crops to grow. So if we're using that much water, we really should be trying to do it in the most sustainable way possible. Why? Because we are using it unsustainably in a lot of locations. So remember, irrigation is the use of surface or groundwater for growing crops. And if we are consuming and using that water in a faster rate that's being replenished, then it's unsustainable. And that's the current state or the current threat to the Ogallala Aquifer in the West. And so the Ogallala Aquifer is an example of a commons. So that means a resource that is owned by no one that everybody has access to. And if we overuse that, that's when the tragedy of the commons take place. And Ms. Fassler did a good example of talking about that last time in terms of the Ogallala Aquifer. So we need to be smart about how we irrigate. So we've got, other than over withdrawing, we've got two other unique problems that I've mentioned: waterlogging and salinization. So let's start with waterlogging. It's pretty basic, pretty simple. It's just when we fill the soil with water, we saturated that rooting zone in the soil. So instead of it being a zone of aeration that is sometimes filled with water, it's permanently waterlogged. It's got water all in there. It's saturated. So while plants do need water, they also need air. The roots need air. And so having that soil filled with water, all of those pores filled with water, the air can't get to the roots and therefore growth is inhibited. And then second, we have salinization. So here's my example of salinization. If I had a pot of boiling water, boiling salt water, if I put salt water in a pot and boil it, the water would fly off, would evaporate, and what will be left in the pot? Salt. Well, that's the same thing that can happen as a response to irrigation. So if we irrigate with groundwater, not with rainwater, but we irrigate groundwater, which has some salt in it, if any of that water stands on the surface of the ground and is evaporated, the salt is left behind. So salinization occurs when the salts in the groundwater remain in the soil after the water evaporates. Over time, salinization can make the soil toxic to plants. So that can happen naturally. Salinization can naturally occur in places, but most of the time it's caused by our over-irrigating a field or poorly draining it. And think about different soil types that we mentioned before and how that might be involved in water drainage as well. So we don't want our soil to be logged with water, and we don't want it to be over-salted, too much salinity. If you think back to the LD50 experiment we did with our seeds, we looked at how different concentrations of salt affect seeds, and you saw some clear effects of salinization there. How do you prevent that or clean it up? It's really hard. Obviously, you can reduce your irrigation. You can use better irrigation practices, but if it's already occurred, removing that salt really takes a lot of time and money to flush it out with lots of water. You could switch to salt-tolerant crops that are more tolerable of those salt levels, but soil salinization is a significant problem with pretty extensive solutions, hard solutions. All right, so thinking of those problems in mind, let's look at these 4 irrigation practices. So we've got furrow and flood. The commonality there is we're just putting water on the surface of the ground. The water is going right onto the soil itself. Spray irrigation is probably what you're most familiar with, like a giant sprinkler system in a field. And then drip irrigation is kind of unique and new. So let's start with furrow. Furrow is like what it sounds. It cuts these large furrows into the field, and then you flood them with water. It's super cheap. Dig a hole, put water in it. Dig a trench, put water in it. The problem is it's a high rate of evaporation and runoff. That means you're losing 33% of that water that could have gone to your plants is now simply evaporating and possibly leaving salt behind, or just running off. So you're losing that water. So a big risk of erosion as well. So here's some other pictures of furrow. You can see the little row crops here. Then in between are these furrows that this pipe is flooding with water. Same thing here. I found this little clip that I thought I'd show just a couple of seconds of. It shows a really unique example of furrow irrigation. It opens up that furrow. Closes that first furrow off. The water flows straight to the second furrow. And as soon as that's full, they'll keep going and going and going. So kind of cool. But does have a high risk of evaporation runoff. And then flooding is very similar, but instead of having those furrows, you just flood the whole field. Again, inexpensive, but a lot is lost to evaporation runoff. And again, same issues of waterlogging, salinization, and then erosion from the field. So you can see here in an orchard, this is some alfalfa. And then we have spray. This is where we have pipes and sprinkler systems and big tools and big equipment, some electricity probably to run those pumps. So it's more expensive, but less is lost to evaporation runoff, about a little less than 40% on average. And you may have seen these large devices, these irrigation devices in agricultural fields, and you can see the water being sprayed onto crops. And then finally, we've got drip irrigation. This is substantially more expensive just because of the labor and the materials needed, but it's really good because only 5% is lost to evaporation runoff. Because of the expense, it is not often used. In a nutshell, it's a hose with some tiny holes in it. So this hose has these little perforation holes in it, and the water simply drips out. So it doesn't gather at the surface to evaporate, nor does it just spray everywhere with the risk of evaporation. It's targeted right into the soil, right next to the roots of the plant. So a very unique system, but it is expensive and not often used. So when you think about these irrigation types, not only should you be able to describe them, but also relate them to different problems such as over-withdrawal of groundwater or aquifers, waterlogging, and salinization. All right, let's shift gears and talk about pests. Pests are anything that's competing with us for our food, for our resources. So we gotta deal with them. We gotta eliminate them somehow or reduce their population somehow. So at the end of this section, you should be able to describe the benefits and drawbacks of different pest control methods. So to get there, we'll talk about some different types of pesticides. We'll talk about how some pests become pesticide resistant, and then we'll talk about mobility in pesticides and how that can have a broader, far-reaching effect than just being sprayed on the field itself. All right, so what is a pesticide? It's just something that's going to decrease crop damage and increase crop yield. Be sure you understand that phrase crop yield, the amount of crops that can be harvested from a certain area. So if I'm using pesticides, I'm reducing the amount of damage to those crops, therefore I'm getting more out of my field. What are some different types I can use? I can start with an herbicide maybe. So an herbicide is going to kill weeds, and if I remove the weeds from my field, there's less competition for light, for water, for nutrients. So herbicides are going to get rid of plants. Fungicides get rid of fungus. Rodenticides get rid of rodents. Insecticides get rid of insects. So there's a wide variety of pesticides we could use. There's also a wide variety of ways we can spray them onto fields or get them on the field. It can be done by airplane. We can spray the pesticides from above, be on a tractor system that sprays it, or it can even be done by hand. The thing that we need to be mindful of if it is done by hand is that this individual has much more of a risk of negative health effects from those pesticides if precautions and proper use are not followed. So I mentioned before the idea of mobility. So if I have a pest in my field and I want to get rid of it, my thought is to spray it on the field and the pest will go away. This target pest will go away. Well, that's my intended path. But what actually happens might be quite different. Some of that might be blown off by wind into another area, might be run off from rainwater and goes into a stream. And once it leaves that field, it can get into other food webs and food chains far, far away from the field that I intended. It may blow into a forest nearby, or it might get into small insects that then biomagnifies up through the trophic levels to large organisms. So we need to be mindful that certain pesticides, especially those that are persistent and mobile, can have some big consequences other than just killing this pest. This is what we saw with DDT. This is Rachel Carson's famous book, Silent Spring, where she warned us about these kinds of dangers. And DDT was particularly bad because it was a broad spectrum pesticide. It killed a wide range of insects, as opposed to a narrow spectrum pesticide that might just target one particular species or group of insects. And so famously we've heard, and I think Ms. Fassler mentioned this before, about the thinning of eggshells in large birds, is that DDT bioaccumulated and biomagnified of the food chain. And one of the interesting results is that it thinned out some of the eggshells. We saw loss of the bird populations. So if we just take a look at this graph, there's another kind of unintended consequence of our pesticide use. On the x-axis is year, and the y-axis is number of resistant insect and mice and mite species. So this means the more we use pesticides year after year after year, we're seeing a bigger and bigger and bigger increase in the number of insects who are resistant to that insecticide or that pesticide. Why is this happening? This is all about adaptation. So remember back in our conversation of adaptation, we talked about how a population with a wide or a very diverse genetic pool, some of those individuals may have particular traits caused by mutations that are beneficial for them to survive. We saw this with the adaptations on the megaplate, the bacteria becoming resistant to the antibiotics. Same thing's going on here, that we are spraying pesticides, some pests are becoming resistant, so we add more pesticides or different pesticides, and we just keep going and going and doing it. That's called the pesticide treadmill. So here's another diagram illustrating the same thing. So we start here, we apply our pesticide. Most of our pests die, but some are resistant, and those resistant ones repopulate. Well, I go out in my field and I think, well, I just did this pesticide, it must not be working. Let me put some more on there. So I put some more on there, but it doesn't have any effect because they're already resistant. So now I have a worse infestation. What do I have to do now? I have to go to a new pesticide, something different, and then the process starts all over and over again. It's a classic arms race. The pest develops resistant, we develop stronger, different pesticides, and back and forth and back and forth. This is a great place to go back and look at Ms. Fassler's conversation in her previous lesson. It was around minute 43. She talked about this great question where there was an experiment about glyphosate-resistant weeds, and around that time she also had conversations about genetically modified organisms like Roundup Ready crops and BT corn. So those genetically modified organisms are a unique way to deal with pests, as opposed to just spraying pesticide on them. We can genetically engineer organisms to be either resistant to pests or resistant to like an herbicide that might kill it normally. So I would have you go back and look at that conversation because you had a brilliant discussion of that. So we're going to pause for a second and go down the experiment pathway. So we know that practice number 4, scientific experiments, forms the basis of some of the parts of question number 1. It says analyze, research, studies, test environmental principles. So we are going to look at an experiment today about fungicide. So I'm going to show you the clip, and after we're done with the clip, I want you to answer these questions. So write these down really quick so that you can answer as we go through. So first of all, I want you to identify the hypothesis. So just jot down hypothesis equals and fill it in as we go through the video. The second one is what is the independent variable, then the dependent variable. The control group. 5 says how might we modify the experiment to improve the findings, and 6, what's the so what? How are we supposed to change our agricultural practices based on the results of the experiment? So let me be quiet for a minute and give you a chance to write down shortened versions of those questions. All right, so I'm going to play the film now. It's about 5 minutes long, and it's going to talk about an experiment about fungicides. And when we're all done, we'll go over the answers to these questions. All right, here
we go. We spray lots of chemicals on plants, fertilizers, pesticides, fungicides, and some of these chemicals have harmful effects on pollinators like bees. There are almost 4,000 species of native bees in North America, but some of these species are declining. As a conservation photographer working on bees, I wanted to learn whether fungicides are one of the reasons our native bees are in trouble. So I visited entomologist Sean Steffen at the University of Wisconsin.
So our work is primarily focused on isolating the mechanism by which fungicides may be harming native bee species.
I didn't see how a chemical designed to kill fungus would affect bees, but Sean explained that some microscopic fungi, like yeast, have an unexpected connection with bees.
So in nature, microbes are everywhere. When bees go out and get pollen from the flower, they bring it back into the nest. So you bring back this protein-rich, wet, sticky, sweet soup. What's to keep it from spoiling in the course of 2, 3, 4 days? It appears that fungi help to preserve these pollen provisions.
Inside the nest, the growing bumblebee larvae feed on this pollen mixture. Sean wants to figure out what kinds of fungi and other microbes these provisions contain. So he begins by dissecting the bumblebee nest in the lab.
We open up these large larval cells, and we get little bits of uneaten pollen. That pollen has fermented. We take it out, and then culture it on a plate.
Culturing microbes from the bees' pollen provisions, in other words, growing them in the lab, allows Sean to isolate the microbes and identify them by their appearance and genetics. He's finding that yeast are a major component of bumblebees' diets.
These larval bees, this is the only food they get. And it appears that some bee species, by the time they finish eating that pollen provision is more yeast than pollen.
So is it possible that fungicides in the environment harm the yeast and other fungi that the developing bees depend on?
There are all these microbes in the pollen that, a lot of those are fungi, and if you have fungicide residue in that pollen, it stands to reason that the fungi would suffer.
And if the fungi suffer, the bee larvae might suffer too. That's the hypothesis that Sean wanted to test. He placed 10 bumblebee colonies, all about the same size, into outdoor cages containing flowers. There was one colony per cage, and in half the cages, the flowers were treated with a fungicide.
The bumblebee colonies could only forage at the flowers that we provided. At the end of the trial, it lasted a month. The control bees, they averaged about 43 individuals per colony. The colonies that were exposed to fungicide residues on flowers, they averaged about 12. We're talking about a profound effect. This is basically what appears to be the first hard evidence that a fungicide, not applied to adults, but just on flowers, caused major colony declines in a single bumblebee species, Biomes impatiens. There's lots of data that show fungicides sprayed directly on adult bees. They're harmless. Those bees are, okay. What we're saying is, well, the pathway by which the fungicide hurts the bees, it doesn't appear to hurt the adult. It hurts the larva. Again, this is just one fungicide, and it's just one bumblebee species.
With thousands of native bee species in North America and many different fungicides used on our crops and ornamental plants, there's still plenty of work to do to understand the effects of fungicides on wild pollinators. But Sean's experiments so far suggest that because of the intimate relationship between bees and fungi, we need to pay close attention to how we use fungicides.
Fungicides are sprayed globally, legally, according to their label, on flowering crops. Some fungicides may be truly harmless, but it's looking like some are not. We're not saying that fungicides shouldn't be banned in any sense, but there are things that can be done. You can spray before bloom, you can spray after bloom. And so our goal is to figure out which ones are not so good, why they're not so good, basically figure out what it is about them that makes them harmful to bees, and hopefully that will inform policy.
So a really great experiment that dovetails perfectly with our course. We have an issue, a problem, pesticides. We can use an experiment to better understand that problem and then make some recommendations about how to change practice. So let's go to the answers real quick. So the hypothesis was that the presence of the fungicide would negatively affect the larva, the bee population. So the independent variable was the presence or absence of fungicide, and the dependent variable was the population, the number of bees in the colony. What was the control group? The control group were the test cages without the fungicides. How might we modify it to get different or better findings? One of the things that came up to mind for me is instead of having some with the pesticide and some without the pesticide, perhaps we have the control without. But then for my experimental groups, I expand it so that I have a low amount of fungicide, a medium amount of fungicide, a really high amount of fungicide. So instead of getting a yes or no type answer like we got here with this experiment, yes, it did affect them, we can actually get an answer that maybe say how might it affect them, to what degree does it affect them, how the concentrations of fungicides affect them. So having more experimental groups will give you more robust findings and can give you kind of different, more robust answers. And finally, how are we going to change farming practices? What was indicated there? Spray the fungicide before or after bloom. So something to think about. All right, so let's switch gears completely from bumblebees and pesticides to meat. So we're going to talk about meat production now. So after this section, you should be able to identify the different methods of meat production and then their pros and cons. So we'll start by investigating a CAFO, concentrated animal feeding operation. Then we'll look at the impacts of meat production on land and water. Talk about free-range grazing is a potential solution. We'll talk about the effects of overgrazing and then how meat production methods contribute to greenhouse gas emissions. So let's start with just some overview of how we eat meat as human beings. So we know that about 40% of the calories consumed in developed countries comes from meat, as opposed to developing countries, only about 5%. Now clearly those are averages, it's not an exact number, but there is a definite trend toward the more developed a country is, the more meat it consumes, because meat is much more expensive and resource dependent than eating vegetarian meals. So if you're going to eat meat, you got to pay more for more land and more resources. So one way we do it in industrialized countries is CAFOs, concentrated animal feeding lots, sometimes called feedlots. So these CAFOs are a quick and efficient method to get the livestock ready for slaughter, meaning it is a lot less expensive and it's a lot quicker than other methods. It gets the cows or the livestock ready for slaughter much quicker, so it's efficient. And it's concentrated, so all the animals are in one location, very dense concentration of animals, and they're typically fed grains as opposed to grass. And that grain sometimes is not as suitable for their diets as the natural grass would be. Because it's so inexpensive, it reduces the cost for consumers for meat. So when you go to the grocery store and buy meat, the cheap price is typically because of the cheap way that it was raised. So let's talk about some problems associated with CAFO. Well, first of all, you've got all those livestock living in one location. You have lots of waste that can easily contaminate soil or run off into surface waters and cause issues such as eutrophication, nutrient pollution, hypoxic conditions, things like that. And because they're so packed together, we do have a risk of disease, a much higher risk of disease than normal, and that's a density-dependent factor. Because the risk of disease is so high, there's typically an increased use of antibiotics to keep the livestock healthy. And just like we saw with the pesticide treadmill, we could have some disease-causing bacteria, viruses, fungi, whatever it might be, becoming resistant to those antibiotics. So this is an example of an FRQ from 2001. We're not going to go over the answer today, but I would highly recommend you looking at this because it's a great experiment, a description of an experiment that took place near a hog farm, and these individuals were studying how this hog farm affected this stream. And so they measured the dissolved oxygen, phosphate, nitrate, and pH. And the questions kind of walk you through an understanding of that experiment. Again, not going to go over it now, but I highly recommend taking a look at that. And again, it's from 2001. All right, so now I want us to contrast that CAFO, those feedlots with lots of livestock, cattle all in one place, to more traditional free-range grazing. So this is a situation in which the animals graze their entire lifetime. So they're not eating that grain or other feed that's been produced. They're eating their normal grasses that they're eating. Because they're not so squished together and concentrated, there's less use of antibiotics. And just think about what their waste can do to the landscape that's used as fertilizer. So it sounds pretty ideal. What are the cons? It takes a lot of land. You have to have space for this to happen. And therefore, it's more expensive to raise this livestock to slaughter, and therefore it's more expensive to consumers. Another unique problem of raising cattle is methane. Cows naturally produce methane as a result of their digestive processes. So that one cow in and of itself making methane, no big deal. No big deal. One cow in the middle of nowhere, no big deal. We have millions and millions of cows. The population of cows in the United States is really, really big because we have so many for meat production. And in fact, it's so much that if we look at the U.S. methane emissions by source, it parallels the natural gas industry. So why do we care about methane? Greenhouse gas. It is one of the main greenhouse gases that contribute to climate change, global warming, climate change. So another little thing to think about in terms of the amount of land required to raise livestock is simply looking at the possibilities of eating less meat. What are the benefits of eating lower on the trophic levels? So it takes about 20% more land to produce the same amount of calories from meat as from from plants. So in other words, there's an environmental benefit for eating lower on the trophic level. So we can take a look at this trophic pyramid here. So this amount of land produces this many cows, and that can support this many people who eat meat. That same amount of land, if these individuals ate from the land, can support more human beings. So there are some environmental benefits of the human population eating perhaps less meat. All right, another con of the livestock industry or meat production is overgrazing. If we have too many animals on the land, we can start using it unsustainably and have some real bad soil degradation. And that's the tragedy of the commons. In fact, this was the example that Garrett Hardin used in his original article about the tragedy of the commons, how multiple ranchers and farmers were putting increasing numbers of cattle on a shared pasture, and the collective effort crashed that system. And that was the tragedy of the commons. Why is that bad? We've got soil compaction. So all those hooves squashing all over that soil a lot is affecting the porosity, permeability, and structural and physical nature of the soil. I have loss of vegetation, and we know the roots hold in soil. And so once we lose the vegetation, we lose a lot of soil to erosion, and we could even risk desertification in some arid areas. So what's the solution? It's rotational grazing. Rotational grazing just means I'm going to graze you in one location, and then I'm going to section it off and put you in another location. And that way the first location has a chance to rebound and regrow. So it is rotating the different pastures that cattle feed in or other livestock feed in so that the older ones can be restored. So that's rotational grazing. All right, now let's look at integrated pest management. This is kind of a cool topic, and it's a much more sustainable approach to dealing with pests. The descriptions we talked about before, there's a pest, spray the pesticide, and that's it. That's all the thought process that needs to happen. I look at the label and say, yeah, it'll kill that thing, kill that thing. Integrated pest management really is very similar to that bumblebee experiment we saw a minute ago, where you have to kind of understand the ecology of the whole system before you make smart choices about how to deal with pests. So to understand IPM, we're going to do the following. We'll first describe the components, what makes an IPM strategy. We'll talk about some pros and cons, and then we'll actually look at a unique unintended consequence, sometimes associated with biological control. So what is IPM? IPM is an ecosystem-based strategy that focuses on long-term management, not eradication of pests. There's a presupposition with traditional pest control that the goal is to eliminate all the pests. I have pest X in my field. I want a pesticide that gets rid of all of that. IPM says, well, that's not the goal. That's not feasible. We want to get them to an economically manageable level. And so the whole purpose, again, is to lower the impact on the environment from pest control. So how do we do this? Well, we first have to understand the life cycle of the pest, understanding how it interacts with the environment. It takes some ecology and natural history knowledge. One of the misconceptions is that within an IPM plan, you never use pesticides. No, you can use pesticides when it's absolutely necessary, but if you do, you plan it out very well, and ideally you use a narrow spectrum pesticide that targets just the pest itself and not other beneficial organisms. So let's look at some actual methods. So IPM methods are sometimes cultural, physical, biological, chemical, as opposed to just chemical, just the pesticides, taking a holistic look. So here's some examples. In terms of cultural, you just change your behavior, change your practices. So for example, intercropping, planting different types of crops right next to each other in a field. Now some of those crops might naturally produce a chemical that wards off pests, or you might want to plant a crop that is really, really attractive to the pest, and so you'll have it eat that thing while your cash crop, the thing that you're trying to harvest, is growing just fine. So intercropping is a way that we just change our agricultural practices to minimize pest damage. You use physical controls, trap them, keep them out, put a big net over your field to prevent birds from getting down into it, or put a fence around your chicken coop from the coyotes getting in, or whatever it might be. But it's physical barriers. Vacuuming is an interesting idea, to take a vacuum and just suck up the pests. Biological, introduce predators. Introduce a predator of that pest that will take care of it for you. I always think, nature doesn't need us to go in and add pesticides to wilderness areas. There's natural habitats that support a wide variety of niches, including niches for predators. So if we can mimic as much as possible nature within our agricultural settings, we can enhance the likelihood that those natural predators will be there because we've mimicked more of a realistic food web. So here's some examples. So farm workers made really sterile male pests, and so therefore they may mate with females but produce no offspring. Planting something for natural predators to exist in, putting in some of that BT corn or the genetically modified organisms that are resistant to pests, sometimes spraying pesticides if we absolutely need to, traps for females. Here's another example of intercropping, molasses grass planted with corn, and it repels some of the corn pests. So you can see it's a much more holistic, varied approach. Overall, if we do that, we reduce the risk that pesticides pose to wildlife, water supplies, and human health. And we also have to consider the fact that this can be more expensive. It's much more complex. The knowledge base alone requires a much more thorough examination of the agricultural setting and the ecology of the area. So I'll end our discussion of biological controls here with the famous example of the cane toad. You may have talked about this in your APES class, but this is the famous example of the toad being brought into Australia. It wasn't native to Australia. It was brought into Australia and unfortunately became very, very, very invasive. It's an invasive species now. It was brought in as a biological control for a grub. It was eating crops, but instead this toad kind of took over. Classic example of how our selected species managed to become a very dangerous invasive species in Australia. There's a great weird documentary called Cane Toads and Unnatural History. If you haven't seen it, definitely find it and see it. All right, so we're going to end today talking about a few sustainable agricultural and food production practices, but mainly we're going to talk about soil conservation and soil fertility, ways in which we can alter our agricultural practices to reduce erosion and to maintain the nutrients within our soil, because those two things are important for agriculture. We need soil and we need fertile soil, so we need to find agricultural practices that will sustain that. So overall, sustainable agriculture looks to avoid or reduce these things. Tillage, or preparing land for planting, is typically very disruptive with the plows and machines that will open up the soil, remove plants' roots, kind of disrupt the microbes that are living in the soil. So tillage is something to consider. We don't want any bare ground. Bare ground equals more erosion. We like to have our soil grabbed onto by roots to maintain soil in the place that we want it to be and not erode somewhere else. We want to reduce our reliance on inorganic fertilizers, maybe think of something like compost, and then also reduce hormones or antibiotics used for livestock. All right, so let's take a look at a few of those. Well, the three famous ones to reduce wind and water erosion are contour plowing, windbreaks, and terracing. You've probably seen pictures like this before, where contour plowing and terracing really follow. First of all, contour plowing follows the contour of a hill as opposed to going straight up and down a hill, and that reduces the effect of water erosion. Terracing does something kind of similar, but it actually cuts into a slope or a hill, these like steps, and this also prevents water erosion or reduces water erosion. To reduce wind erosion, we use windbreaks or shelter breaks, and that's just going to lower the impact of wind blowing across a field, so big hedgerows or rows of trees. Another way to reduce erosion is to think about using perennial crops as opposed to an annual crop. So an annual crop grows one year, I harvest it, and I get rid of it. So it only lives less than a year. And when I get rid of it, by taking it out, I'm exposing the soil and I'm increasing the chances of erosion. If I use a perennial crop, it lives many, many years and can be harvested many, many times before it dies. So again, just a chance to lock in the roots to the soil a little bit longer. No-till agriculture, so traditional tillage would, like I said, be pretty disruptive to the soil, but no-till agriculture, which is a type of conservation tillage, does preparing for planting in a way that is much less disruptive to the soil. And some of these residues from the previous year's crops can sit there and act almost like green manure that can add fertility to the soil. Now, when I first heard of no-till farming, in my head I couldn't imagine how you would plant seeds without tilling. I'm not a farmer, I'm not from an agriculture area, so in my head I was imagining like someone having to go through and poke their finger down into the soil to plant the seeds. But this little clip really did a nice job of explaining that to me.
So how exactly do these farmers plant without plowing? Most use no-till planters, which are designed to slice through plant residues from previous harvests while minimizing soil disturbance as they plant the seeds for their crops. Here's how it works. Pulled by a tractor, a no-till planter uses thin, rotating discs to make a narrow slice through the plant residue and into the soil. Next, a tube places the seed at an appropriate depth in the soil. while a second wheel gently presses or firms the seed into the soil to ensure proper seed-to-soil contact.
Pretty cool. All right, and the last little strategy we're going to talk about is liming. So one thing that farmers have to study about their soil is the pH, how acidic it is. Acidic soils pose some unique problems. One of the problems of acidic soil is that it can liberate or make soluble more aluminum, and that aluminum can actually be toxic to plant roots. And it might disrupt the range of tolerance, or it might be outside the range of tolerance for the soil microbes. We know how important those are for soil health. And so if our soil is too acidic, one thing you can do is to add limestone to it. That's rich in calcium carbonate. And what that's going to do is it's going to reduce that acidity. It's going to raise the pH. Again, it reduces the risk of aluminum toxicity, improves microbial activity, and it helps to kind of maintain that soil's cation exchange capacity, the soil's ability to hang on to nutrients for plants to be able to use. Here's another nice picture of this farmer putting lime on his fields. All right, let's do a quick multiple choice question. An integrated pest management approach to pest control emphasizes which of the following? Take 12.5 seconds. So we would want to reduce crop damage to an economically tolerable level. That's one of the goals of IPM. All right, so what did we do today? We looked at irrigation methods, pest control methods, meat production methods. So we talked about standard practices here, and then we talked about IPM and other practices of agriculture that put us in a much more sustainable zone. And we also practiced scientific experiments, practice number 4 with our bumblebee fungicide study. And that's actually what I'm going to leave you with for homework tonight is a great FRQ that asks you to practice your experimental design skills. This is all about pesticide X. So this is asking you to devise an experiment to determine how toxic that pesticide is to small fish. And then it asks you to talk about IPM a little bit, and it finally asks you to talk about 2 agricultural practices that increase crop yields. So when we're all done, be sure you go back and pause it here and read over the questions, and Ms. Fassler will go over that next time. So again, by this Friday, please reach out to the URL below if you yourself or you know anyone else who needs some solutions about connectivity and internet access or mobile tools in preparation for the exam. All right, apes, happy birthday, and I'll see you next time.
Hi guys, welcome back to our virtual AP Environmental Science classroom. It's great to virtually see you today. I'm Ms. Fassler, coming to you from Marshfield High School in Marshfield, Wisconsin. We're going to start our warm-up by taking a look at the pesticide experimental design question that you worked at for homework. Let's begin by reviewing the prompts that you started with here with the background information. The active ingredients in many pesticides are chemicals that kill organisms such as insects, molds, and weeds. Proponents, people that are pro the use of that insecticide, claim that pesticides improve crop yield and thus protect land and soil by reducing the conversion of forests and wetlands to croplands. Opponents of pesticide use claim that pesticides degrade water and soil quality and that other modern agriculture techniques and practices are responsible for increased or improved crop yields in recent years. Before we look at the questions, just remember a great strategy that you want to use on the national exam is just take a minute and read that entire prompt before you jump in and start answering the first question. You really want to know where that question, how that question is progressing from one topic to another, and how all of that is going to integrate. And trust Dr. Sowell and I when we say that if you take that few minutes and really process and think about the question, take some notes as you're reading it, the writing of it itself, your final answer is really going to come together quite easily. So we start off with letter A with our experimental design part of the question. Design a laboratory experiment to determine whether or not a new pesticide, product X, is toxic to minnows and small fish. For the experiment you designed, be sure to include all of the following. For 1 point, you needed to state a hypothesis, and there's 2 criteria you need to earn that 1 point. First of all, the hypothesis has to predict the relationship between product X and minnow health, and the prediction needs to state which direction or that impact is going to be. For example, I could say that an increase in the concentration of product X will increase minnow mortality, or I could say does decreasing exposure result in increased survivorship of the minnows? Kind of saying the same thing a different way. You could also have stated it as a null hypothesis. Concentration will have no effect. If you've not used a null hypothesis in your classroom, don't worry about it. You would never be required to state a null hypothesis. Next, we're going to, for 1 point, describe the method that you would use to test your hypothesis. And in order to get this point, notice that you need 3 experimental groups, or at least 3 different treatments. I'm guessing I always kind of prompt my students to use even more than that to be on the safe side. And at least one of those is a group that's not been exposed to product X. So what we mean by that is I need to have a group that got no exposure to product X, and then in this rubric, I needed at least 2 other concentrations so that I don't just have no product X and a lot of product X. I'd like to hone in a little bit more on what concentration was harmful. If you go back and watch the earlier video on toxicity, we go through a lot of review of this as well. For the next point, you had to identify the control. Remember, the control in your experiment does not get any exposure to whatever that independent variable is. So my exposure in raising the minnows might have simply been the normal pond water that those minnows lived in with no product X at all. And finally, identifying the dependent variable. If I change or control the concentration, what will change as a result of that? And you probably said something about minnow health. You may have said how many minnows die, or some way to assess the health of the minnow. Letter B, describe the experimental result that would lead you to reject your hypothesis. In other words, if something happened where there was no relationship between chemical X and minnow mortality, I would therefore reject my hypothesis. Letter C, one strategy for dealing with agricultural pests is integrated pest management, or IPM. For 3 points, you had to describe IPM, and as part of that description, give 2 specific pest approaches that are part of that integrated strategy. So for the first point, it was sort of the definition of a characteristic of IPM. I'm guessing a lot of you said something about a combination of either physical, chemical, or biological. Notice you needed at least 2 of those strategies. You could also have talked about IPM being used to reduce or eliminate the use of pesticides, or to reduce pest populations to an acceptable level. Remember that I want to not kill every pest, but kill enough of them that I still have a yield that I can harvest from my crop. The other 2 points then are for giving a specific approach. And so you could have gone with some type of physical barrier. You could have gone with some type of chemical approach other than the pesticide itself, like spraying a pheromone, those chemicals that the insect naturally releases to attract predators. If I spray that pheromone, all the insects are attracted to that, and then I can trap them or catch them in some way. So there's a lot of different statements that you could have made about specific strategies. Next, for 1 point, an environmental benefit of IPM, it could reduce the amount of pesticides that I use. It could reduce the amount of runoff from those pesticides. It could reduce the erosion. It could prevent the killing of non-target insects like honeybees. And finally, describe 2 agriculture practices other than those involving pest control that increase crop yield. And one of the things we're really going to focus on today is that task verb describe. We're going to dig into that really deeply. And I want you to focus on the part of the rubric here that says what you needed to do to get that point. There's a difference, remember, between identifying an agricultural practice and describing an agricultural practice. And I know that a lot of my students, when they read this, they think they just have to describe what contour plowing is. But what you need to do is describe how that practice would increase crop yield. And when you look at the rubric, it appears as if it's almost just an identify point. A lot of the description of how that that practice would increase crop yield isn't necessarily spelled out. The rubric is just this bulleted list of possible responses. It's not the entire 10-page essay of all those descriptions. So for example, I could say that applying fertilizer is a way to increase crop yield, but I wouldn't get the point until I said adding fertilizers, which improves the nutrient content of the soil, will increase crop yield. So we're really going to focus on that described term today. So let's take a quick look at where we're going. Just remember that your exam is open notebook on May 18th, and you want to check out that website that the College Board has provided really great tips to prompt you how to get organized for this. In addition to what Dr. Sowell and I are sharing with you, I just pulled out 2 of those little tips to focus on today. Your class notes are better than internet searches. Dr. Sowell and I are making sure we're providing the information for the review for you, that you don't have to go out and look for it in any other source, that you're not really sure if that's good information or not. And this is very important. Collaborating with others is not considered acceptable open notes, and you really want to read about the criteria associated with exam security and the consequences for violating that. So where we're going today, I misspoke the other day. I said we were going to get through Unit 5 in 3 lessons. It's actually 4. So this is our third of 4 lessons on Unit 5. And what we're really looking at today is kind of a problem solution. What are the problems associated with the way we harvest trees and some viable strategies to mitigate that? What are some problems associated with how we harvest fish and some solutions or strategies for that? Really focusing in on these 2 big ideas. How does our use of natural resources impact the world, and why it's often so difficult to achieve sustainable resource use? I really want to focus on, as well as describing, like we just did with that IPM question. Notice our skill number 7 here is all about solutions. And the letters sort of scaffold at what level I need to be able to demonstrate that skill. Everything from just describing a potential solution to describing the advantages or disadvantages or unintended consequences, and then going even a little bit further to justifying why my proposed solution is the best solution. And maybe it might be picking one solution. Are you going to go with IPM or a different strategy? So let's dig in and remember that we're really focusing on that describing and justifying solutions. That's going to be our main focus today. Before we get into clear cutting and some of those practices, I just want to make sure we're all on the same page about why we cut down trees to begin with. And that looks a little bit different in the developed world, like in the United States and Germany, where that has a lot of logging. For the most part, our logging practices are pretty sustainable. We've been doing this a while. We typically value good research in how our forests are managed and apply those best practices. That's very different in the developing world, where they will clear large tracts of forested land for agricultural land or pasture land. And another big reason for that is for charcoal production. This is a picture that I took kind of almost downtown Nairobi in Kenya, in East Africa, and they don't have an energy infrastructure. We're going to go into energy next week, but they don't have a line that delivers natural gas to them, or they don't plug a stove in for electricity. Often what they do is they just walk down to this little kiosk down the street here and purchase a bucket of charcoal, and that came from cutting down trees. So if you have a campfire and the next morning you go out and there's some little hunks of charred wood left, and you could probably spark that and get that to burn again. That's pretty much what this charcoal is. It's a very unsustainable and really inefficient source of fuel. So in the developed world, we practice, like I said, for the most part, pretty sustainable forest management. The main reasons we would cut down trees would be for wood products, everything from construction material to paper products that we make, and as a management technique for maintaining a healthy forest ecosystem. So let's just do the quick review. What is a clear cut? It's the removal of all the trees from a tract of forested land in one area. It leaves a big opening, very obvious. It's a pretty broad term that can really be used to describe a lot of different kinds of clear cuts. There's a really big difference between a small clear cut that I might make, even though it classifies as removing all the trees from a forested tract of land. If it's a 20 hectare or a 50 acre clear cut, that's not going to have near the environmental impacts as a very large clear cut like this one is going to have. And we're really going to focus on these really negative impacts of these very large clear cuts. This is not a logging operation where somebody's manually going in with a chainsaw and cutting down individual trees. And that might happen in a small clear cut. This is where very large logging equipment is going through and at a very large scale removing all those trees very quickly. So that's the reason that we clear cut. It's quick, it's easy, and it's certainly the most cost effective way of removing trees. So we're going to spend a little bit of time looking at some of these other advantages and disadvantages of the way that we remove trees. So some of the impacts of clear cutting. If we want to know what the impacts of taking all these large trees from a big tract of land is, we probably better start with just a real quick review of the ecosystem services of forests, because that's where I'm going to get that described point, is really showing that I understand the actual impact in a lot of detail. So we have these provisioning and regulating and supporting and cultural ecosystem services. And it's very obvious when I look at this image of this big clear cut and I look at the ecosystem services, there's no longer that vegetation there anchoring the soil. So I get a large amount of erosion. I remove carbon dioxide from the atmosphere. I'm no longer removing that carbon dioxide, so I'm no longer sequestering carbon or moderating climate. Trees produce oxygen, which everybody needs for survival, and they provide habitat for wildlife. So those wildlife can rear their young and have nesting sites or denning sites and hide from predators. Now we're really going to dig into that describe aspect then. I want to look at, keeping in mind those ecosystem services, some of the impacts of clear cutting. And a couple of those really integrate the idea of how forests and the water cycle connect together. So if I increase soil erosion, I could have an increase in stream temperature because those soil trap particles trap heat. When the sun shines on that stream, after that water is run downhill from that area I clear cut, if there's a lot of solid particulate soil in there, when sun strikes that surface of that water, instead of being able to penetrate, it's caught by those solid particles and really heats that surface water. It could increase flooding in the watershed because I no longer have that infiltration, or like I'm seeing in the diagram here, I'm no longer allowing that water to seep in and recharge groundwater. I could have a loss of biodiversity because of a loss of habitat, and I could accelerate climate change because of the loss of carbon sink, or the fact, remember in slash and burn agriculture, they burn the remains of that wood, put the nutrient ash on the soil, but the minute I burn that wood, that carbon dioxide goes into the atmosphere. Even if I cut those trees down and leave all of that slash and the small limbs and everything on the ground, then they're going to decompose, and that carbon is going to be put back into the atmosphere as either carbon dioxide or methane. So if we want to manage our forests sustainably, we want to look at other techniques besides clear cutting. So the idea of sustainable yield just ties in perfectly. What we're going to do is look at ways that we can log, because we need the resources. We have to find a way to get them in a sustainable way, and then we'll move into some other strategies to mitigate once I've actually cut down the forest. So just remember that idea of sustainable yield really is going to apply when we review that idea of selective cutting. Practice of selecting certain trees within my stand. In clear cutting, that big piece of equipment comes through and plows out all of those trees. But in selective cutting, I'm saying, okay, here's how many trees I can take, but still leave a viable stand of trees. And I'm going to want to make sure I have an uneven age stand or a multi-age class stand left. In our simple diagram here, there might be different trees of different ages and sizes or different species, so that I am still fulfilling all the ecosystem services of that forest. Sustainable yield. I can harvest some trees, I can get economic profit and fulfill my need for the wood products, but I still have an intact forest ecosystem. And one of the ecosystem services that we tend to forget is that cultural ecosystem service, that value that I get from having wild places. In this area that's been selected selectively cut. There's a couple tree stumps here and there, and a logger's going to go through and mark which trees they're going to take. It's a very prescriptive process to know how many board feet of lumber I need to get out of there, what it's going to cost me, so I can still make a profit, but still leave an intact ecosystem. And I would still go hiking or cross-country skiing or set up my tent in camp. I could still hike or I could still hunt and really provide all the services that forest did before I cut it. And there's plenty of trees left of different ages to regenerate. Another really good sustainable forestry technique to reduce the amount of trees that we cut is to find alternatives for those wood or paper products that we need. And one of the best ways that we can find alternatives is for what we call pulpwood products that we purchase. We all know that paper comes from trees. Toilet paper comes from trees. And a lot of cutting trees down to make a lot of toilet paper these days. So what they do is they take wood and they kind of cook it down and they add some chemicals and they just really focus on the strong cellulosic material, the fibrous material of that wood, and ultimately turn it into paper. So I could find alternatives. I could use a composite wood. Here's an example of a decking made. There might be some wood fiber in there, but it's integrated in with even perhaps recycled plastic for that composite wood that's got a number of different kinds of particles mixed together. I don't know if you know what particle board is. You do, but you may not know that you know it. I take like little wood chips and products and press them all together, low quality leftover kind of wood scrap, and press it together and make boards of lumber, if you will. Well, I really have to take trees that maybe took 40 years to grow, and I cut those down, and a lot of the impacts of that, I can grow straw annually, really easy to harvest, and I have the same fibrous material from that. Bamboo, a lot of you may be aware that bamboo is a very rapidly growing plant, so I can harvest it each year, and it really quickly rejuvenates. So we can buy toilet paper made from bamboo rather than trees that took 40 years to grow. Hemp is another fibrous material. We think of hemp as rope. During World War II, there was a big push to get farmers to start producing hemp for the war effort, because again, what I'm looking for is a cellulosic fibrous material that I can capitalize on that rapidly growing fibrous plant that instead of trees that take a long time to grow and harvest. Palm leaves are being used for disposable paper plates, but again, instead of a tree, I'm using a rapidly growing plant. Please remember that when you have to provide solutions, I can never provide a solution that just simply says, well, don't cut down any trees or ban a practice. What is appropriate is replacing part of that practice with something that's more sustainable and alternative. The other really good solution that we want to talk about is making smart, educated consumer choices. So if I'm going to buy wood products, if I'm going to build a house or buy lumber for a project for my home, I can look for wood products that have the Forest Stewardship Council logo. So if I am running a timber stand and selling wood products, I may work with this organization and they're going to come out and inspect and make sure I'm using best practices for sustainable management. And they're going to say, you're a good company. We're going to certify you so that as a consumer, I know that I'm supporting a sustainable practice. And we always can reduce and reuse and recycle our wood products. I can recycle reclaimed wood. I can go to a secondhand store to buy a piece of furniture rather than buying a new piece of furniture. I could refinish an old piece of furniture rather than replacing it with a new one. So let's now move into sort of the next phase of sustainable forestry. We just talked about all the things that could reduce the amount of trees that we have to cut, do selective cutting and using less and making best choices, do substitution. Well, now what happens, we have an area that has been pretty damaged by deforestation and we want to reforest it. And I'm going to show you three kind of broad techniques that you could use as solutions. One would be nonprofit organizations like the Nature Conservancy. They certainly do work globally, but in the United States, their reforestation project is Plant a Billion Trees. And they have a number of projects scattered throughout the country where they have found areas that have suffered from significant deforestation, areas that may have lost 90% of their native timber stands. Maybe it's an area that has some endangered species that really needs to have that habitat reforested so that the species can rebound. The next method for reforestation could be a private landowner. Working with the American Tree Farm Association as a private landowner, I might still need to harvest some timber from my land so that I can make a profit and pay my taxes. But the Tree Farm Association is going to help me manage that. They're going to help me go in and say, well, here's about how many trees you could take. Here's what age we suggest. So that's a really good option. Or this really interesting concept called debt for nature. It works in the United States with a landowner that might have forested land, maybe wetland. Maybe it's a farmer that has part of their land that they own in forested land surrounding their fields. And in the debt for nature program, that landowner enters into a conservation contract. And they say, I agree for whatever period of time that I am not going to develop this land. I'm going to keep it as a forested, intact ecosystem. And in exchange for that, I get a reduction of some of the debt that I might owe on my land. It's a really good way to keep land for struggling landowners in their family and reduce the debt load that they have. This actually was applied on an international level in 2010 with the United States and Brazilian governments. They owed us some money that we had borrowed them, and we forgave some of that debt in the agreement that they put some of that land in conservation or agreed not to cut certain areas of land. It's a solution or strategy that I think a lot of times gets a little bit underlooked or underutilized, if you will. So we understand that tropical rainforests are a global resource. We all need and benefit from the maintenance of forested land in the Amazon forests of Brazil. So it is a value for other developed countries to try to assist these developing countries that really just need economic growth and they have a resource that they can harvest. We should just pay them to say, don't cut your trees, to value that global resource. And then we have grassroots efforts like the efforts of Wangari Maathai. You may have heard of her. She was a Kenyan woman who actually won the Nobel Peace Prize for her work with the Greenbelt movement in Africa. And aside from just planting ultimately over 50 million trees, she got individual women to take little tree seedlings and go out and plant them. And a more long-lasting legacy, I believe, is that she really got these women, a new generation of women in Africa, to embrace the rich resources that they have and preserve them for their future, for their children's generations. Certainly, we see evidence of this all the time. And one of my favorite quotes of all times from Margaret Mead: "Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has." And that's how we as APES teachers are inspired sometimes to keep going, because we know that you guys embrace that as students, embrace that idea as well. So before we go on to do a quick check, I want to share with you a very positive story. Remember, parts of Unit 5 here can get a little bit overwhelming with some of the unsustainable practices that we talk about. So I'm going to share just a couple minutes of a really exciting, positive story that's happening at the grassroots level in the Darien Gap. So we're going to go to Panama first.
Among endangered tropical forests, this one is unique. This forest sits in the middle of the longest road on Earth, the Pan-American Highway, which runs from the tip of Alaska to Tierra del Fuego, Chile. The forest is called the Darien Gap because it is the only interruption in the highway. Within this region lies Darien National Park. Throughout history, Darien's rough terrain has shielded it from the outside world. But today, as tendrils of development spread from the road, pressures mount. From illegal loggers to migrant ranchers that are pushing deeper into the gap, slashing and burning to create pasture land. This threatened forest is home to wildlife and indigenous people who have lived here for thousands of years.
Soy Carlos, soy enviado de la Región. Actualmente formo parte del sistema de información geográfico indígena, que mapeo territorios.
The maps being produced with the support of scientists of the Rainforest Foundation are powerful tools for indigenous communities. They use them to get legal titles for their land, to create sustainable land use plans and to monitor their forests as outside pressures close in on the gap.
Cuando vemos que estos tipos de amenazas para nuestros pueblos, para nuestros territorios, no tener un título colectivo nos hace hipoteca cualquier situación que nosotros queramos hacer.
If you want to watch the rest of it, it really is a great story and very inspiring. Now, they work with the International Rainforest Foundation, but they involve the entire community, young people, women. They understand the value of maintaining forested land for clean water. They work with the Rainforest Foundation to say, can I clear, they still need to grow food. Can I clear small tracts of land, but do it in a sustainable way? And really in the bigger scheme of things, giving them the power to take control of their lands and keep those invading forces off. So really some great cool things happening in the Darien Gap. So let's do a quick check for understanding of the forestry concepts that we talked about. After intensive logging, most of the trees along a stream have been removed. Which of the following water quality changes would most likely occur downstream from logging? You may not have known this, that's why I really wanted to focus on that increase in temperature. It's sort of there's a sort of a one more leap before I get to that increased temperature. So cut down the trees, sediment erodes, that sediment traps additional heat. Which of the following environmental effects would most likely result from the clear cutting of boreal forests by industrial logging operations? And obviously that would be letter A. I think they kind of specified boreal forest, and probably not clearing land in the boreal forest. It's just not a climate capable of producing a lot of food. I think we have one more here. Sustainable use of forests in the United States would likely be encouraged by, and again, that's a pretty easy one as well. Look at the verbiage there. That's one of the reasons I wanted to put this question in. If I have to describe the difference between clear cutting and selective cutting, or justify why one of those is a better practice than the other, this idea of an uneven age stand, that I'm cutting trees of various sizes and ages. I want to go through just a little bit of a guided practice because, gosh, we haven't even looked at a data table or a graph yet today. So here is an image that shows me changes in forest cover. So let's use our I-square technique, identify, interpret, and then we'll answer a couple questions. My x-axis is years from like 2000 to 2001. My y-axis is annual forest loss in kilometers squared. So that's an area value, the area of loss of forested land annually. So in 2000 to 2001, that's an annual cycle, I lost about 7,500 square kilometers of forested land. In Indonesia, this is Brazil, and there's some statistical values represented here that represent that trend line. I want to really focus in on this value. This is the forest loss annual increment. So my x-axis is time, my y-axis, annual forest loss in kilometers squared. Now let's do an interpretation. What does this mean to have an increasing or a decreasing trend in forest loss? Is forest loss occurring faster or slower as time goes on in each of these scenarios? So in Indonesia, my forest loss annually, every year, I'm losing 1,021 square kilometers of forest land. In Brazil, that's a negative, well, it's a negative slope to my line. I can see it's downward trending. In Brazil, my annual forest loss is negative 1,318 kilometers square. So let's see if we can make a statement then that answers this. Increasing forest loss is a positive slope. It means there's a faster rate of forest loss, whereas the decreasing forest loss, that negative slope, says that each year there is a decrease in the area of forest loss. If I just like really quickly glanced at these graphs, I might say, oh, Indonesia is seeing an increase in forest land and Brazil is seeing a decrease, but it's looking at forest loss. So the question I might be asked about this is, using these figures, make a claim about which country is at the greatest risk for forest loss in 2013. And that would obviously be Indonesia. We would predict that in 2013, they would have lost another 1,020 kilometers square. Now, I can't say that Brazil is gaining forested land. I don't know what they're doing from this graph in terms of reforestation, but I'll qualify that because it's hard to say now. During this period of time, Brazil was seeing 1,318 kilometers squared less land cut every year. They were decreasing the amount of deforestation. All right, now let's go on to the second half of our lesson. Oh, wait a minute, we have just a little bit more on forestry. Not too much to say. In terms of pest control, all that you learned about IPM with Dr. Sowell and integrated pest management for agriculture, all that same biological, physical, chemical, same things apply in forest management. Another thing I can do for pest control is removal of trees. This is an example where a small clear cut in an area of pine trees that have been infested with the mountain pine beetle. We talked about that in the invasive species lecture. This might be a time where that is justified because the drawbacks associated with that clear cut are outweighed by the fact that I don't want that beetle to spread to other trees. So I could take out individual infected trees, or I may have a small clear cut. We also have to talk a little bit about the role of fire in managing forest ecosystems. Remember that a periodic fire can be beneficial. And this is where, again, I'm really going to focus on that described term. A periodic fire can be beneficial because it reduces fuel load. That's an identify point. I have to make sure I spiral all the way around and say, why does reducing fuel load provide for a healthy forest ecosystem? Well, it prevents a more destructive fire that might take out more species. Periodic fire can be beneficial because it kills trees infected with pathogens. But I've got to make sure that I describe why killing trees is beneficial. Well, I can prevent it just to spreading to other trees. Recycles nutrients back in the soil, which improves soil fertility, opens the forest canopy, which stimulates the growth of new species that like sun, protects communities from extreme fire and reduces the economic impact of those disasters, improves habitat and stimulates new growth, which provides habitat for a diverse number of species and provides conditions necessary for certain species of trees or wildflowers because they need heat to release their seed and promote their growth. I'll just mention a little bit about prescribed burns, both in a forestry setting. The state of California has embraced prescribed burning because they had a lot of fire suppression and built up a lot of that fuel load. And so that's that their problems are being exacerbated by climate change, which is causing death of more trees, which means there's more dry wood and more fuel for a severe fire. So in order to prevent a more severe fire, I can go in periodically and start a fire on a small controlled scale to burn up some of that fuel load that's laying on the forest floor, all that dead wood, so that if a fire accidentally starts, it's not going to have as much fuel and I can contain it a lot more easily. And the positive note here, the forester is monitoring the new growth of trees after that prescribed burn. We also remember that point about how some species need fire in order to release their seeds. Well, that's a natural part of prairie management where fires are set on a rotating few-year cycle basis. It's really what created grasslands to begin with. Remember, these are some of the most fertile ecosystems in the world, temperate grasslands. And the reason is because fire would normally start either by lightning or Native Americans. We now know that in order to maintain or restore a prairie, we need to integrate that as it's an essential part of the management tool of that prairie. And that's how we end up with all of the beautiful blue stem grasses and purple cone flowers and all the beautiful prairie flowers that need that heat to release their seeds often. So let's do another quick check for understanding on that by looking at a logging question. State is considering opening an area of old growth forest on state land to logging. Officials debate the best way to log the forest. One official advocates for clear cutting 1 hectare, that's a small plot, in the middle of every 20 hectares of an intact old growth forest. The official says this pattern will maximize biodiversity while still allowing allowing the harvesting of timber. Explain how the pattern of biodiversity, explain how the pattern could produce more biodiversity than the old growth forest alone. Well, I could say things again that there are some species that like sunlight. Not all species like that old growth forest habitat. So I provide new species with new niches, some of those early succession communities. And another official wants to harvest timber in a more sustainable way. The official wants to assess individual trees and remove only the most economically valuable trees that would help maintain the forest ecosystem. Propose a logging technique that would best meet these two goals. Survey says selective cutting. So we still are harvesting. I'm still meeting my economic needs, but I'm leaving an intact stand of trees. Now we're going to shift gears and go to harvesting fish. So some of the causes of overfishing, they're really pretty simple. We just are not fishing at a sustainable yield, right? We're taking more fish than and not leaving enough fish stock population to repopulate that. Our large-scale fishing techniques can seek out every fish in an area that we're fishing and leave nothing for repopulating that. The reasons for that, unfortunately, are pretty straightforward. It seems like there's just a lack of global willpower, a lack of global legislation and enforcement of that legislation. And as a result of that, the number one cause of overfishing is illegal fishing. It's estimated that illegal, unreported, or unregulated fishing, and unreported is important because if a country says, oh, we're only harvesting this much, it may look like they're harvesting at a sustainable rate, but they're kind of lying about their catch. Altogether, that's over $36 billion a year. So let's dig into this a little bit more deeply. Certainly, one of the impacts of overfishing is loss of biodiversity because, I gotta make sure I say why overfishing causes a loss of biodiversity. I'm removing a species that might disrupt an entire food chain. I may have a trophic cascade based on the species of fish I remove, and a large number of my fish are often caught by, I catch non-target species through gill nets or drift nets or other fishing techniques that I use. Another impact of overfishing is loss of food security for people that are fishing on a more sustainable or subsistence level, where they're catching enough fish through small-scale fishing techniques to feed their family and maybe sell a little bit, and the destruction of ecosystems caused by these many different fishing techniques. But trawling, I think, is an easy one for kids to remember, where I drag that heavy-weighted net along an ocean floor. I can destroy an entire coral reef. So not only am I netting fish, there's a lot of bycatch, that unintended species, and I am potentially destroying the habitat that's going to further prevent those populations from rebounding. Some of the solutions, again, they sound kind of easy. We need international legislation and international enforcement and accountability. But here's, just like with forest products, I can make really smart choices as a consumer. And I like this because this is something that you can do directly or even try to influence your parents to make some sustainable choices. And just like we had that label for sustainably produced wood, there are labels that I can have for sustainably caught fish as well. And different species that are the best fish because their populations are strong and those ocean fisheries are appropriately managed to fish that I really should avoid and try not to eat at any cost because of the current state of that fish supply. One solution to large-scale loss of ocean fisheries is aquaculture. And in its simplest form, aquaculture is simply rearing animals in an enclosed area rather than catching them in the wild. I have this I have a fish farm that I create where I'm raising fish. And as you can see from the graph, fish farming has really taken off. When I look at this graph, I can see that my wild capture really is kind of flatlined for decades. The amount of fish that we're capturing from the wild really hasn't increased. And as a scientist, one question we might have is, well, is that simply because aquaculture has taken off and I don't need to fish as much in the oceans, or there just isn't as many fish left? This also should raise a question for us about, okay, it looks like we've really quadrupled the amount of aquaculture production. This is tons of fish harvested. Are there any impacts associated with that we should be aware of? So here are essential knowledge statements that we'll take a look at in terms of aquaculture. This is, if you remember when you studied this in your class, we really can describe these large aquaculture operations as CAFOs on the water. You talked about CAFOs with Dr. Sowell, that concentrated animal feeding operation. All of the problems associated with the CAFO on land correlate to problems associated with large-scale industrial aquaculture as well. So those problems, first of all, as we could tell from that previous graph, the industry has grown and it isn't very regulated. It has grown so fast that the ability to sort of monitor what's happening and where those fish farms are springing up is very challenging. There's a very high density of fish in a very small area, just like the CAFO, that leads to disease transmission and often the use of antibiotics. It leads to a fish poop, and they're all fishing and pooping where all those fish are in that concentrated area, and that accumulates waste and dead zones in that area. Those wild fish are often genetically modified or bred to grow really, really fast, really, really quickly and get to market. So if those wild fish escape, they're often very aggressive breeders, can breed with native fish and reduce the biodiversity in my native fish stocks. And if we look at where these fish are being raised, where most of the really skyrocketing growth of aquaculture is happening, it's happening in countries that may not have environmental regulation or regulation that adequately monitors their food supply. So if I don't have any water pollution control laws, I could have raw sewage running off and entering the area where my aquaculture, where my fish farm is. I could have heavy metal contamination. All kinds of different toxins could be present in the environment in which that fish is being raised. And I, as a consumer, may not know that. I want to seek out the origin of where that fish is sourced from and make some smart consumer choices about aquaculture versus wild caught fish. I don't want to give you the impression that all aquaculture is bad. We as consumers need to make an informed decision about where that farm raised fish is coming from and the conditions in which it was raised. And that's why we have that certification. To alleviate some of those problems, we do have sustainable aquaculture. This is this land-based fish farming where fish are raised in these tanks. That water is constantly being recirculated, cleaned, and put back in. So it's a sustainable use of water. It's growing fish in an environment in which I can control the quality of the water and the waste, and doesn't have the impact on coastal ecosystems that some aquaculture does. So we covered quite a bit for today. Let's take a quick look into a couple of questions on aquaculture. Have to have another graph. This graph shows worldwide catch of orange ruffy, a type of wild fish caught, and this represents the amount of fish caught in tons from 1977 to 2011. And this is giving me my quantity of fish. It's a pretty easy graph to interpret based on the data which of the following fish practice solutions would best promote sustainability of the population. And again, establishing quotas for the number of orange ruffy that are caught. You want to have that term sustainable yield in your notes, because if I simply said I could fish orange ruffy at a sustainable yield and only take enough that I leave enough breeding stock to repopulate, easy point. Which of the following is true of farm-raised salmon? This is kind of specific. They're often infected with parasites and sea lice. It's a pretty interesting story about fish farming in British Columbia, up in the Pacific Northwest, where these huge fish farms have emerged. And kind of long story short, this parasite, this sea lice, always has infected salmon to a small degree, but their life cycles are such that when the fish is in the open water and it could be infected with lice, the lice just aren't dead. There's not many there. Just die with their life cycle. And remember, fish migrate, swim back upstream to their original area to spawn and mate. So what happens is that in order to get back to their original spot where they're going to spawn and mate, they have to swim through the area where these fish capos are, and all the lice have accumulated in that area. We have one more question here. The farming of fish such as salmon at aquaculture facilities poses a threat to marine ecosystems because And that's something that we just talked about as well. So just a quick debrief here. Remember, we wanted to really focus on describing. We looked at problems with harvesting trees solutions, problems with harvesting fish solutions, but we really focused in on how I accurately and sufficiently do that describing to make sure I actually don't say just here's the impact, but how does that impact do what it does, and justifying, presenting solutions, listing advantages and disadvantages, and justifying those solutions. Hope you guys are hanging in there. We're kind of getting close to the end. We're going to have lots of time to review before that May 18th date. Here's your homework for tonight. It's about the island of Hispaniola, that is both the countries of Haiti and the Dominican Republic, and some issues that they're dealing with deforestation, and then just a little link into human population to keep you going on that. So hope you guys are hanging in there. Just remember to look at that sheet, the sheet about best tips and practices for online exam taking. Start getting your notes organized, focusing on those skills, and I will see you next time. Enjoy your wrap up with Unit 5 with Dr. Sowell tomorrow. Take care, guys.
Hello, AP Environmental Science students. Happy Friday. And if you're watching this later, hope you have a nice Friday. So my name is Dr. Sowell, and I teach APES in Jacksonville, Florida. So quick reminder about our exam date and times over here on the left-hand side of the screen. And on the right-hand side, you can see a description of the 2 FRQs that are going to be on the exam. So worth looking at. Another reminder, I know Ms. Fassler and I both mentioned this the last couple of days, but a really great resource is the College Board's update page about tips for success on open book, open note exams. I would definitely take a look at that. I know from my students, I've had them take a look at this and really think about what kind of notes they're taking during these review sessions. And then finally, a final reminder on your AP Classroom, when you log in, you will see a new place that says practice answering free response exam questions. You now have access to a few more that you may not have seen before. And it's a place where you can practice writing them, looking at the rubric, see how you did. Just another resource to get you ready for the 18th of May. All right, so let's go over the homework from last night. This is the 2017 question number 3 FRQ that Ms. Fassler assigned last time. And this is all about the island of Hispaniola, which houses the Dominican Republic and Haiti. And there's this unique way to visualize the border between the two. You can look at rates of deforestation. So question A said, provide one reason why deforestation commonly occurs in a less developed country like Haiti. So you could have said things about clearing for agricultural land or to produce charcoal. Ms. Fassler showed a really cool picture the other day of a charcoal stand somewhere in Africa and how that charcoal is used for heating and for cooking in homes. You could have said for building materials or just clearing land for human use, roads and homes and stuff. So let's look at a student's response and see what they said. Deforestation is more common in a less developed country like Haiti because their economy and government isn't getting strong or developed enough to put deforestation regulations in place. This means that there are less consequences to companies that clear cut forests. There you go. One reason why that might be happening. All right, here's another example of the strategy. So here we're looking at the strategy to reduce that problem. So this person said a realistic strategy to reduce deforestation in these less developed countries is to subsidize companies if they don't clear cut, but instead cut down trees in a scattered, more sustainable manner. This way, the companies can still use lumber, but the trees will grow back in a manner that ensures ecological resilience. Absolutely. So putting in regulations or laws or subsidies that promote more sustainable forestry practices. An interesting two down here at the bottom, reduce population growth. That would be one strategy to reduce the demand on the forest. Or ecotourism, shifting the revenue from chopping the tree down to going visiting the tree in a park or six. All right. So now this will be 1 point for this person. Let's go to B. So B says deforestation can affect water quality. Identify one change that can occur in the water quality of streams within a watershed that has been deforested. Explain how deforestation can lead to this change. So this is an identify and explain. 1 point for identifying the change in water quality and 1 point for explaining how deforestation caused that change. Right? So you could say an increase in water temperature because there's less shade. There is an increase in turbidity because there's more erosion and runoff. There's more nutrients because of loss of vegetation reduces the amount of assimilation of nutrients and that runs off into the stream. Same thing for pH and DO. So let's just see what this person said. One change that can occur in the water quality of streams within a watershed that has been deforested is that the water quality will be bad because there are no trees to filter and clean the water, and there will be more water because the trees also absorb the water, but without it will flow straight down. So unfortunately, this did not get any points. Describing the water quality as just bad is too generic of a term, too general, too vague, and it doesn't sound like you've taken an APES course. An APES student would be able to describe water quality in ways other than just bad. And then the second part of their answer here talked about the amount of water, not the quality of the water. C. Identify 2 environmental benefits other than those related to water quality of maintaining forest ecosystems. Remember, many times on an FRQ question, there will be this clause that says other than blah, blah, blah. For whatever reason, that's a nice place for our eyeballs to sometimes scan over. So slow down and read your questions really carefully. So other benefits from the forest might be to deal with carbon, excess carbon in the atmosphere. It releases oxygen. It's involved in biogeochemical cycles. It reduces erosion. Lots of things other than water quality. So this person said forests are a vital carbon sink and producer of oxygen. They help to reduce greenhouse gases and produce clean air, reducing impacts of climate change. Trees and forests provide habitats to important species that may provide a variety of ecosystem services. Okay? 2 things identified. Carbon sink, habitat. This person said for the same question, 2 environmental benefits of maintaining the forest ecosystem is that it provides a place for animals to live, their habitat, and it will increase or keep the biodiversity. Well, unfortunately, that's only worth 1 point because that idea of habitat and biodiversity is really almost considered part of the same idea. It's not a whole separate idea, so only 1 point there. All right, then the next one says identify and discuss one factor in a less developed country that could significantly or that could contribute significantly to a change in life expectancy similar to what occurred in Haiti from 95 to 2015. So in those 20 years, we saw the life expectancy in Haiti really increase. Why? You had to identify the factor and then how that contributed to an increase in life expectancy. So increase in healthcare, turned into prevention of early death because of vaccines, or fewer pregnancies, so fewer children resulting in fewer maternal deaths. So you had to identify a factor and then discuss how that factor contributed to life expectancy, not just describe that factor. So this person wrote the adoption of advanced medical techniques and technologies could increase the life expectancy as well as reduction of harmful pollutants. So this is only getting 1 point for the advanced medical technologies improvements in healthcare. The second clause here, as well as reduction of harmful pollutants, that's a whole different idea. That does not explain how that factor contributed to life expectancy. So this person said an increase in healthcare in a less developed country can greatly increase the life expectancy in that area. When people take better care of their health and have more access to medicines, they are able to live longer and fight disease more effectively. So there are 2 points. An increase in healthcare, there's our one, and there was a good description of how that factor increased life expectancy. So a good, robust, full answer there. E says identify and discuss. So same pattern again. One economic or cultural factor in a less developed country that could contribute significantly to a change in the fertility rate, similar to what occurred in Haiti during these 20 years. So the fertility rate went from 5.2 to 2.7. Why? A lot of things in terms of education and equal opportunities for women, industrialization and economic development. So again, you had to not only identify that factor, but discuss how that factor dropped the TFR or the fertility rate. So let's look at a student sample. Increased education for women would increase the number of women in the workforce. The more women in the workforce constitutes a lower fertility rate. Another possibility is increased access to contraception. Now this is only worth 1 point because they did identify an increase in the women in the workforce, but instead of going on to explain how that contributed to a drop fertility rate, they jumped to a completely different idea about contraception. So they get the 1 point for the identify, 0 points for the discuss. All right, so let's jump into some new stuff. So we're going to wrap up Unit 5 today. We're going to start looking at mining, the impacts of urbanization. We're going to look at the concept of an ecological footprint. And finally, we'll look at some solutions and methods to reduce urban runoff. And just for the purposes of how I've organized this, I'm not going to go in this exact order. I'm going to jump around a little bit, but we will cover everything. All right, so what you need to know. 511 is footprints, ecological footprints. You need to know what a footprint is and what are the things used to measure it. So to get there, we are going to describe what goes into a footprint and then talk about what that can tell you about consumption and waste, both the per capita lens and the per country lens. So what's the footprint? It's a way to measure the human demand on the environment. It's really looking at the amount of land and water you need for the resources you use, as well as the amount of land and water to take care of the waste you generate. And this can help be a really useful tool in understanding, are we using our natural resources in a sustainable manner, and what could we do to change? It's nice a way to quantify things that for a lot of us seem very nebulous and unquantifiable. It's a way to give us a lens on our consumption. And what we can do is once you find out an individual's ecological footprint, you can simply multiply that by the total population and get a generalized footprint for the entire country. Because again, this is not just about population. We talked a lot about population before in the previous unit. So our environmental issues are not simply we got a lot of people. That's part of the problem. But it's also that certain ones of those people, certain individuals, consume and generate more waste than others. And we'll look at those differences here. So before we do that, let me give you a short animated little clip of what footprint is, ecological footprint.
Our human activities consume resources and produce waste, and nature needs to have the capacity to meet these demands. The ecological footprint is a way to measure our human demand on nature. Every one of us has an ecological footprint. The footprint represents the impact of a person, a household, a city, a business, or a country on nature. Things like food, energy, transportation, goods and services all contribute to our ecological footprint. The footprint is expressed as the amount of land and water required to produce what we consume and to absorb the waste we generate. By measuring the ecological footprint, we can assess the pressure our lifestyle puts on the planet. This helps us to manage our ecological assets more wisely and to take personal and collective action.
So because this is something that we can quantify, it may be something that might show up on a data table or a chart. So it's good to look at some actual numbers for this. So this is usually measured in hectares per capita per person. So for example, the global average, the average human being right now uses about 1.7 hectares or about 4.2 acres. The average US citizen though uses 8.1 hectares or 20 acres. Compare that to Spain, which is about half of that. And then we look back again at Haiti, and the average individual in Haiti has 0.7 hectares or 1.7 acres. So again, some wide variation. And you can start thinking of reasons for that in terms of economic development, standing, or the location of the demographic transition where they are, and then population. So this is a nice graphic of the per capita. So the darker numbers indicate a darker per capita ecological footprint. So you can see some pretty dark colors here in North America and in Europe, and some parts of the Middle East and Australia. And then we can shift and look at that into a graphic form, more of a data chart or a graph. So you can see Qatar is around 16, so this is per capita. So the average person in Qatar is having the largest ecological footprint. And then it kind of goes down. You can see the United States is around here, Estonia is in 10th place. So this is the top 10 countries with a per capita ecological footprint, the average citizen in those countries. And then we can shift to the per country view and some similar patterns, but you'll notice that the country of China, India, Brazil, those are a little darker than they were before. And that's just simply because of population. So if we look at the per country ecological footprint, China is huge. And then if we go down the roll, we go all the way down to United Kingdom. So this is per country. Why do we see these differences? Just population size. So the average citizen in China may have a smaller ecological footprint than some of these, but there's so many people in China that the overall footprint is greater. So that's why it's useful to look at it per capita and per country. So one of the things I would highly recommend you doing, if you haven't done it already, is find one of the online calculators that will do this for you. This is the one that I happen to use, footprintnetwork.org. It's a really easy one. And what it does is it just asks you a series of questions, I don't know, 20 questions or so, and eventually it'll generate this number for you, 4.3 Earths. And that just means if everybody acted like me, then we would need 4.3 Earths to sustain everybody. That means I'm using way more than what is allotted to me. And then it'll also give you more quantifiable numbers, so 7.3 hectares of land for my resources and my waste. And then it'll also break it down into categories like cropland or fishing grounds. Really interesting stuff on the carbon footprint. So definitely go through there, play around with it, click on the solutions button. Really cool learning tool to kind of explore some of the solutions that you could pose to decreasing your ecological footprint. So speaking of footprints, let's look at mining. The human action of mining for minerals and resources and fossil fuels has a huge footprint, a huge impact on the environment. So by the end of this section, you need to be able to describe some general practices of mining and then describe ecological and economic impacts of natural resource extraction through mining. So to get there, we're going to describe surface and subsurface mining. Now I'll say here, there are lots of types of mining, and where you mine and what country you're mining in radically changes what mining looks like. I have cherry picked a few mining practices to highlight, but by no means is what I'm getting ready to talk about an extensive look at mining. Just in the time constraints of this video, I had to kind of select some parts. So we'll describe surface and subsurface, and then we'll look at the idea of high grade and low grade ores and how that affects resource use and pollution. And then finally, we'll look at some broader environmental impacts of mining. So let's start with this question. What are we mining for? Why do we do mining? Why do we mine? Well, first of all, we're looking for metals, copper and iron, and cobalt and gold. Tons of different metals are used in our everyday products. The computer or the cell phone you're using right now to watch me contains some of those metals. So those metals are essential in making a lot of the products that we use every day. We might be mining for non-metal minerals. One that I like to think about is phosphate salts. Here in Florida, we have lots of phosphate mines, and phosphate is mined out of the ground and used for things like fertilizer. And then we could also be mining for fossil fuels, coal, oil, and natural gas. When we get into the energy unit, we'll talk a little bit more about some other oil and natural gas mining practices like hydraulic fracturing, but today we'll focus on coal mining here. And then when we look at these impacts of these metals or non-metal minerals or fossil fuels, we need to think about their entire life cycle. So not only is there an impact from mining, but we've got to refine and process these materials, we've got to transport them, we've got to use them, we've got to dispose of their waste. So again, think about the entire life cycle associated with mining and the use of these products. All right, so before we get into how it's mined, we need to look at what's mined. So if I'm mining for, let's say, copper for say, I'm not simply going to dig a hole in the ground and find pure copper just waiting there for me to take out. The copper is going to be embedded within rock, or it might be gold, or whatever we're looking for is going to be bound typically within rock, and that's called ore. Ore is a rock that contains a concentration of a mineral that can be profitably mined and extracted. So this rock has something in it that I want to mine out of it. Therefore, the combination of rock and target material, that's called the ore. And that can come in two categories: high grade ore and low grade ore. It's pretty self-explanatory. The high grade ore has a lot of the stuff I want, as opposed to low grade ore has less of the stuff I want. So if we look at two rocks of the same size, two pieces of ore of the same size, high grade ore is going to have more of the material I'm looking for than low grade ore. Why does that matter? Because of this. I want you to imagine if you're going to start to mine for something, where are you going to go first? What are you going to mine first? You're going to mine that really accessible high grade ore. That's going to give you the most profit. So it's typically going to be more accessible, and then that piece of rock is going to have a lot of what you want inside of it. So that's what you're going to go to first. But eventually, that resource is going to be depleted. It's going to run and get lower. So then what I'm going to have to do is look for low grade ore, pieces of rock that has less of my target material. And because it's low grade, to get the same amount, I have to mine more ore. So if we look up here at this high grade ore, it had 9 pieces, let's just say. But down here, the low grade ore only had 3 pieces each. Therefore, I needed to mine more land and do more mining and use more energy to extract the same amount of mineral. So there's an increase in use of resources, an increase in the water or the waste and pollution that I generate because I'm now having to go to lower grade ore. So let's look at the 2 big categories. The 2 categories that we're going to talk about today are surface and subsurface. And we're just going to start with surface mining. So surface mining is done when the ore is closer to the surface, and we can basically dig it out by standing on the surface with machines. Excuse me. And so one of the ones we're going to look at a strip mine. And this is an example of a strip mine here. You can see these long strips back and forth. So this dark material is being mined. And when it's time to move over here to this next layer, all of the rock above will be removed and placed down into the trench or the strip that's already been mined. So it's probably easier to explain it from this picture. So if we look at this picture of the ore, the thing that I want, the rock that I'm trying to mine is down here at the bottom. But unfortunately, it is covered with lots of rock and soil and earth. That's called the overburden because it's over what you're trying to get. That's a burden to remove. So we're going to take this overburden off and put it to the side, and now we can access the ore. Once we've accessed this ore and it's time for us to move over to this next section, we will take this overburden and put it in this strip that we've already mined, and now we have access to this ore. So it's these strips or consecutive areas in which we take the overburden, put it in the previous trench, mine the ore. And again, that material is called the overburden. So one of the things that I'm from Florida, I don't see a lot of mines, big coal mines or copper mines. That's not something I see a lot. And I remember first learning about mining and being amazed at the scale of the machinery that's used. These massive machines are invented to do this work. Now those machines are obviously running on fossil fuels probably, and the amount of greenhouse gases and pollution that's made from those machines is probably rather significant. So this is a little clip of a coal mine that really shows you the extent of the machines used.
Josh Gardner drives one of the trucks that work these pits. It's a 6:30 a.m. shift change. Time to go to work.
Hey, where, Josh? Hey, what's up? Hey, it's you.
Our ride is basically a dump truck on steroids. It stands over 2 stories tall and weighs almost 200 tons. But it seems dwarfed by the shovel at the base of the pit.
So if we pause here, let me move that out of the way. You can kind of see this is the coal that they're trying to get at, and everything above that would be the overburden. So right now, this is the coal that's being mined out, and the overburden that was up here is now deposited over here.
That's our first bucket in.
It's like a small earthquake.
This actually is telling us how much weight we have on it. The first bucket was 68 tons, and then the second one, 60.
Looks like it's raining coal.
So we got 174.
3 bucketfuls, and we're on our way. One truckload like this can produce enough energy to heat a home for more than 40 years, or run your television for the next 2,000 years. All day long, Josh drives in a big loop, filling his truck with coal, dumping it, filling it up again. In a single shift, he can haul 8,000 tons.
Very cool. I just like to see the extent of machines used. And that can give you a little sense of the environmental impact of some of these mining practices. Things like the construction of roads or the burning of fossil fuels. There's a lot of machinery that has to move in and out of these locations. Those need roads. That's obviously going to cause habitat loss or fragmentation. And then we've also got all of the dust and erosion that's happening. So a lot of dust in the air, particulate matter pollution, and then erosion. If we're removing vegetation, remember roots hang on to soil. And once those roots are gone, the soil is more prone to wind and water erosion. And then if some of those materials escape through surface or through rain or surface water, they can actually contaminate our surface waters or groundwaters. So that's surface mining. Now let's go way below and do subsurface mining. So this is when the target resource is simply too deep to use those machines we just saw. And therefore, mines have to be dug downward and then horizontal so that the human beings and the machines can get down there. It's much more expensive and much more dangerous for the individual workers. They have to be concerned about fires and explosions and mine collapses in that tight confined area way down below. And then there's also a particularly sad consequence for some coal miners and other miners that the dust can get into their lungs and cause a disease called black lung that's very dangerous. So subsurface mining has some unique health and environmental aspects to it. All right, so we've seen a little clip of surface. Now let's look at a little clip of subsurface. But what you should notice is the machinery that's involved is just as extensive. It's just way down below. All right, it is not working. I will see if I can put that in maybe next time we go. It's a cool little video. It just shows the machinery down below the levels of the earth. All right, let's keep trucking then. This is looking at mining in a less developed country. So one of the things that we need to think about is that in less developed countries, we may have mining operations that are more human-based and less mechanized. There may be less regulations involved. And so one of the unique things about gold mining is sometimes individuals will use mercury to separate the gold from the ore. And that mercury is obviously a poison that can cause mercury poisoning, or if you study metabolic disease, something very similar. So let's just look at a gold mining operation that will look radically different from those heavily mechanized versions we just saw.
Bettina Moulter's hands can't stop shaking as she bands a mix of gold and mercury in a mining area in Migori, Western Kenya. She's done this for the last year, and she says her body tremors and slurred speech are some of the effects of mercury pollution. The mercury she bands up can remain in there for up to 1.5 years, and in water that goes up to 11 years. An estimated 1,400 tons of mercury from small-scale mining like this is released every year.
The tremors are sometimes very serious, especially if I'm burning the stuff when it's raining. Sometimes I can't even move.
That's why there's a global campaign headed by the United Nations to stop the use of mercury in unofficial gold mining, where alternative machines are still too expensive for miners like those who are here.
What they're doing now is separating the gold from sand and other particles using mercury. It's a tedious process. They spend hours doing this, and in a good day, one can produce on average a gram of gold.
So both of those videos you just saw, the surface mining in the United States and this more small-scale mining in Africa, the goal is the same, is to separate that mineral from the ore, but how we go about doing it, and the human and environmental impacts could be very different depending on where you are. So let's look at some wastes of mining. So remember, if we have our ore here and our target mineral, this little orange triangle, this is what we want. Well, the blue stuff is not what we want, so that's the waste. We got to get rid of that. And those are called tailings. That's what's not desired from the ore. And those can be either stored in large piles or in tailings ponds. And why do those need to be stored and taken care of? Well, they could contain lots of this fragments of rock might have heavy metals in it. We wouldn't want those heavy metals getting into our waterways. And also could have chemicals used in the extraction process. So these things have to be carefully monitored. And if there is a break in these dams or these piles kind of get exposed to rainwater and runoff or even into surface waters, that's going to cause a lot of environmental and human health impacts. Last year, there's been several large tailings dam failures recently, but there was a large one last year, and it had to be caught on camera. So you'll actually see the dam breaking, and you can see all the tailings liquid starting to flow out. So sadly, that could cause loss of life, but also has environmental consequences as well. So we really need to be careful of those tailings, how we store them, because we do not want them to affect the environment or to harm people. And another unique aspect of pollution that comes from mines, especially abandoned coal mines, is called acid mine drainage. And this is when water flows over those tailings or flows over some of the coal that are in old mines. It can actually pick up some of that sulfur in the rocks and create sulfuric acid. Well, that's bad enough by itself, but then that acidic water can leach out heavy metals. So now you have bodies of water that are not only acidic, but have heavy metals in them. This is a news clip from a news station in Ohio that looks at some of these abandoned coal mines and the effects of this acid mine drainage.
You may not know this, but almost 90% of Ohio's electricity comes from coal-fired power plants. And while the newer coal mines are regulated, those old abandoned ones from a century ago are leaking toxins into our streams.
Meteorologist Ben Gelber is just back from the Wayne National Forest in southeast Ohio to show you some big concerns about what those old mines are doing to our environment.
Dwayne, the Ohio Department of Natural Resources estimates there are more than 6,500 abandoned underground mines in eastern Ohio, and toxic mine discharge is still turning streams orange, a century after the mines were closed for good.
My parents always told us to stay out of the creek because it was sulfur water. It was a pretty orange color.
Dale Duvall grew up in the old coal mining community of Carbon Hill, which is along Monday Creek that winds through the Hocking Hills past Nelsonville to the Hocking River. Duvall remembers what it was like in the summertime, diving into a large, cool pond on the other side of the hill.
When you would swim in it, when you would come out your bathing suit, and you would smell like sulfur.
This is the opening to an abandoned coal mine, the Essex mine, with toxic metal sludge. This is where the Sycamore Run comes through and carries pollutants into Monday Creek.
So while there may be stronger regulations on newer mining practices, some of these old abandoned mines that have been kind of forgotten could result in this acid mine drainage. So let's just do a quick check for understanding. And this is a graph that we need to analyze. So remember, whenever you see a graphical representation of data or a data chart or a data table or any kind of graph, slow down and really analyze the pieces and parts of it before you try to figure out what story it's trying to tell. Where I start always, and this is something that we've talked about before with the I-squared method, is look at the axes. The axes start the story off. So the first thing I see on the x-axis is years from 1900 to 2020. On this side of the y-axis, I see mill grade, % copper. So I know that the word grade probably relates to low grade or high grade, and that's how much of the target material I want. So here it's copper. So down here, this ore has 0% copper, whereas this ore has 2% copper. Right? So I understand that y-axis. Over on the other side, it's milled ore. How much ore has been taken out of the ground? 0, 60. All right. So now that I kind of understand what's being measured, now I can look at the relationship. So the ore mined has gotten greater and greater and greater. So the overall trend is as the years have progressed, I've just simply mined more ore. But also at the same time, the grade or the percentage of target material, which is copper, has gotten lower and lower and lower. So if we think about being able to describe that relationship, they're kind of inverted from each other as one goes up, the other one goes down. But then if we had to explain it, this is where that understanding of high grade ore and low grade ore comes into play. That as I mine more and more of the high grade ore and I deplete that resource, what's left is lower grade ore. And to get the same amount of copper, I have to actually mine more and more of the ore. So a good example of how you might be presented with a graph and then describe the relationship, describe how the variables are interacting with each other from the graph itself, and explain why that's happening. All right, so let's move from mining to urbanization. So after this section, you should be able to describe the effects of urbanization on the environment. So to get there, we're going to look at urbanization's effects on resource use and pollution. We'll talk about how that might impact climate change. We're going to look at a unique problem of urban areas, which is impermeable surfaces. Then look at another unique problem called saltwater intrusion. And finally, we'll look at the concept of urban sprawl and how that affects the environment. All right, so first of all, let's define urbanization. Urbanization is the overall trend or shift from rural life to urban life. A misconception point here is that urbanization doesn't mean the size of the city. Okay, urbanization just means that trend of a country moving from a more rural population to a more urban population. So there's more and more city life. It's not talking about actual square area here. That's more sprawled. So what does that really mean? Well, that shows a shift in development and resource use. So for example, if you're living in a rural area, probably your occupation, your way of living is more directly connected to natural resources and harvesting those natural resources, as opposed to an urban area where you're not. Why is that? We have industrialization, we have economic development, the demographic transition. So the nature of the jobs themselves change as we move from an urban to a rural, or from a rural to an urban society. So as about 2008, that's when, as a planet, more people were now living in cities than in rural areas. So we still have more people, living in rural areas, obviously, but at this point in our history, more people live in urban areas. What does that do in general? Well, clearly, a shift to urban living increases our fossil fuel use, not just for electricity generation, but for industrialization, for vehicle traffic, transportation, and all of those greenhouse gases getting into the air are, especially carbon, is affecting climate change. So here's a unique problem called saltwater intrusion. This happens when urbanization happens in a coastal area. This is happening in some parts of my state here in Florida at this time. So before human beings were around, before urbanization started here at the coast, the pressure of this freshwater was enough to push the saltwater to this boundary. So here's the saltwater, here's the freshwater, and the reason this boundary exists is because there's enough freshwater to just push it to this line. This is a little brackish zone here where it's a little mixed. But then we urbanized the coastal areas, and along with urbanization, you need drinking water. And so here in Florida, a lot of our drinking water comes from our aquifer underground. So these wells are drilled into the ground and start drawing up water. Well, what that does is it starts to pull the salt water to this boundary further and further inland, and unfortunately sometimes that can contaminate our wells. And so the salt water intrudes into not only our drinking water, but our agricultural irrigation as well. So a specific urbanization problem here on coast. So I said before that urbanization was the general trend toward living in urban areas and city areas. Then there's a separate concept called urban sprawl, and this is the kind of oozing out of the city, just getting bigger and bigger and bigger and bigger. So the definition is kind of complex. Let's just read it here. It says the expansion of human populations away from central urban areas. So we're moving away from these central urban areas into something like this, which is low density. So there's fewer people per area here. The density is lower. Monofunctional. Think about that. Think about if you walked in this one square block of this city, you might see houses or apartment buildings, stores, hospitals, schools. You would see a lot of different functions in this one block. Whereas here, all I see is houses. It's monofunctional and usually car dependent. This, if you live here, you don't need a car. There's public transportation. There's walking. Everything is more compact. Whereas here, you would need a car. So it's the shift to this from this high density multifunctional area to really low density monofunctional. So multifunctional, monofunctional. Why is the shift? There's an increased use of cars, so more roads can take us out there. And more wealth equals more choice. So as incomes increase, people have the choice to live elsewhere. There might be cheaper taxes, or you might have better jobs in the suburbs. You may just want a big yard, you want more property. There might be better schools or less crime, or simply for aesthetics. So there's a lot of reasons why this urban sprawl happens. And in some places, that urban sprawl is not sustainably planned. It just kind of oozes out, like I said. But some places are really doing smart growth, where that growth of the city is more planned out for less of environmental impact. We'll talk about that in a second. All right. So this urbanization and urban sprawl, one of the most unique things we really don't think about a lot is just the amount of impervious surfaces we make. So all of these roads and buildings and sidewalks and parking lots, if those were not there, rainwater would simply infiltrate into the ground and percolate down. It would get back into the groundwater. But instead, we've kind of sealed it all up, and so the water now moves in a very, very different way. How does it move and what are the problems? Well, clearly, it's not going to allow our aquifers to recharge. Here in Florida, we need rainwater to infiltrate the ground to recharge our aquifer. But if we kind of put the Tupperware lid all over the land and kind of seal it up, the water can't get in there. So where does that water go? It runs off. So stormwater runoff. And if that water is not channeled somewhere, either into a gutter system like this or into a retention pond like this, we could have a risk of flooding. Okay? So think about the water that travels, or the rainwater that travels down the street where it goes into this gutter. It's picking up lawn fertilizers and oils and cigarette butts and plastic pieces. So we can really get heavy contamination of surface waters just from this runoff over urban streets and rooftops and things like that. So in Unit 5, it explicitly says that this unit explores human activities that disrupt ecosystems, but it also explores methods to employ to reduce the impact. So we talked about these problems with impermeable surfaces. Now let's look at a few solutions. So the first one is permeable pavement. So they have invented pavement that will suck up the water. So if you look over here on the left-hand side, all the water that's falling on this street is simply pooling up and collecting. It's not getting back down into the ground, as opposed to this permeable pavement, which allows the water to be absorbed. So I found a clip of a company that makes this pavement, and it shows this large dump truck full of water being poured onto the pavement. Well, if this was traditional pavement, the water would just pool up here and get deeper and deeper and deeper and eventually run off and carry whatever pollutants that are on the parking lot into waterways nearby. But instead, the water is absorbed into the pavement.
From
experience using permeable paving today is basically I've done a lot of residential block paving permeable systems. This is the first time I use a top mix permeable paving. So yeah, quite a bit of experience using permeable materials before. Top mix permeable materials is so good as in the way it can deal with the water in such a quick amount of time.
Very cool. So the water just gets absorbed right down into the ground.
I'll see.
So another solution to reducing urban runoff is planting trees. So planting trees in urban areas not only provides other benefits like aesthetic benefits or clean air benefits or shade benefits, it also can help with this stormwater runoff. So the water, instead of simply running off, might actually get down into this grassy area where the tree is planted, and the tree can take up some of that water and get rid of it through evapotranspiration or just using it. Or it can just let it get down into the groundwater again. So there's some definite benefits of this urban forestry idea to deal with runoff. Another one is increased use of public transportation. And a great example of that is Curitiba, Brazil. So if we have more public transportation, that means we would in theory have less vehicles on the road and therefore the less need for more roads which are impermeable. So shifting really heavily to public transportation decreases the need for more and more roads. And Curitiba, Brazil did a really interesting thing. As the city was growing, it grew the city along its transportation hubs, its public transportation routes, so that no matter where you live in the city, you could get on a piece of public transportation and get somewhere else. This would be kind of the opposite of that sprawl where it just kind of oozes anywhere it wants. The city has purposely planned their city's growth based on their public transportation lines, and therefore there's less need for cars, less need for roads. And then finally, this kind of dovetails with that conversation, but sometimes cities can increase their population and capacity by growing up as opposed to out, the opposite of that sprawl. And so that's going to shift everybody to areas, like I said before, where you're going to have mixed land uses, different zoning. Zoning is how a city decides what goes where, whether it's business or a residential area. So if you have smart growth, maybe you have mixed land uses so that your school and your job and your grocery store and your house are all within walkable distances from each other. And different modes of transportation are available in terms of biking or walking. But overall, it's building up, not out. And obviously, that's going to reduce the permeable surfaces and reduce the problem with that stormwater urban runoff. All right, so let's do a quick check for understanding here by looking at an FRQ. This is from 2015. This is FRQ number 4. And it starts off by saying the term urban sprawl describes the expansion of cities into rural areas. This phenomenon has occurred around the world and has had economic, health, and environmental consequences. So the first question says, A, describe 2 causes of urban sprawl. So just take 20 seconds or so and jot down some ideas of describing causes of urban sprawl. All right, so you may thought of things that we mentioned on that list just before. So changes in transportation use, lower gas prices, better roads, that might be able to get you out of that city center into a suburban area if that's your choice. Lower cost of living, higher taxes in the inner city, or the quality of life category of, having a yard and less blight or less crime. So there's lots of reasons that people would shift from living in the city center out toward the suburbs. So this person says, A, urban decay. A lack of money and infrastructure in inner cities causes problems with crime and job opportunities. These problems cause people to move away from the urban areas and into more rural ones. Okay, there's one. Increased prosperity. As income in countries such as the U.S. increase, people seek more land and larger homes. This desire for more property pushes people to the suburbs for more room to live. So just 2 good descriptions of why we would see that sprawl. So the second one says, B, discuss 2 human health effects associated with sprawl. So we describe what sprawl is. Now we want to think about human health effects. Take a few seconds to think about that and we'll be answered. So you may be thinking about the air pollution in city centers that might be really problematic. That air pollution might cause respiratory problems, obesity because of less walking around. You're more relying on cars and other forms of transportation. Hearing loss from noise pollution. That was a really interesting thing. Reduction in disease spread in lower density areas. That's a human health effect. Let's take a look at this person's response. Urban sprawl means that cities are spread out further. Increased use of automobiles to get around means an increase in air pollution. In big cities, photochemical smog causes many health issues such as asthma. Boom. There's a good discussion of the air pollution problem. Second, increased automobile use means that less physical activity for the average person. When they drive places, people don't walk or get as much exercise. This can cause obesity, heart disease, and cancer, among other things. So there's a good description of that shift in activity level. So this next one is the last one we're really going to look in detail here because this asks you to look at a graph. Again, I'm going to ask you time and time again, when you see a graph, slow down, deconstruct the graph, look at the pieces apart, and then step back and say what story is it trying to tell you. So let's do that. So let's start with the axes. So we're going to look at the x-axis down here. Density, persons per hectare. So that means over here, it's really not crowded. Over here, it's really crowded. It's high density of people, low density. Okay, I got that. On the y-axis, it says relative annual per capita petroleum use. So annual. So yearly per person crude oil or crude petroleum use. That means down here, I'm hardly using any crude oil. Up here, I'm using a lot of crude oil. So now that I got my axes under control, now let's think about what story that line is telling. That means somewhere like Hong Kong, it is very dense, but the average citizen is not using a lot of crude oil. And then over here in Houston, for example, not very crowded at all, very spread out, and this person is probably using way much more fossil fuels than someone in Hong Kong. So that's a good describe answer to that. But the explanation would come into play that probably if you're living in Hong Kong in a highly dense area, you're using less fossil fuels because you're walking a lot of places. As opposed to if you live in Houston, you're relying on cars a lot to get around from place to place. So I'm going to jump to the last part here. E talks about highway systems, and this asks you to describe 2 methods to reduce harmful effects on wildlife populations. And this is where the conversation about wildlife corridors might come into play. We're building roadways around habitats. So not only do we need to think about housing and transportation, but literally the road that we're building is taking over natural habitat areas. All right, I'm going to jump through this for time's sake here and kind of go to our summary. So we talked a little bit about mining, talked a little bit about urbanization, discussed what a footprint is, an ecological footprint, and then we looked at those solutions to reducing urban runoff. And several times today we looked at graphs and tried to interpret what those graphs were telling us about the problems. So your homework for tonight, no homework, happy Friday, no homework. So have a really good weekend and we will see you next week. And just as a final reminder, today is the last day to communicate to the College Board if you have connectivity issues in terms of internet or mobile tools, or if you know someone who does. So please be sure to contact them by today, please. Thanks again, have a good afternoon, and I will see you next time, mates.
Hi, everybody. Welcome to the AP Environmental Science Virtual Classroom. I'm Ms. Fassler, and I teach in Marshfield, Wisconsin. So if you did the live lecture with Dr. Sowell last week, you didn't have any homework. It was no homework Friday. So just a quick overview of your exam. I haven't seen this before, have you? Our 2 questions that we'll be writing on May 18th, and then a reminder to check out the College Board Tips for Open Note tests. Really encourage you to do that. Dr. Sowell and I will be, throughout this week of review and during our practice exams, we'll really be trying to get you to hone in on visualizing what that exam day is going to look like and what it's going to look like to sit down with all of your notes in front of you and helping you organize that. So today, last week we spent almost the whole week on Unit 5. Lots of information in that land and water and human impacts. This week we're going to spend 3 days looking at energy resources, and I'm going to do the first 5 learning targets there. Dr. Sowell will pick up tomorrow with renewable resources, and then we'll have a 3rd day for wrap up. Obviously, in this kind of introduction, and we'll dig in a little bit to fossil fuels, we really focus in on big idea number 1 on energy transfer. Energy conversions underline all ecological processes. So we saw this recently in the review when we looked at the 10% ecological efficiency rule and how energy is transferred from one trophic level to another. Well, in this unit, in Unit 6 on energy resources, we're going to look at energy systems that take energy resources and put them into a usable form of energy for us, but we still have to look at the second law of thermodynamics. There are 3 big objectives I have for today then. Describe how patterns of energy consumption function different throughout the world, explain why the availability of natural energy resources depends on a region's geologic history, and justify the use of different energy resources based on economic, ecological, and human health factors. So we're going to start right away with this discussion of global energy resources, and we're going to focus in on this essential knowledge statement that the geology of an area determines where fossil fuels are located and which fossil fuel that is, if I have coal, oil, or natural gas. Let's see if we can kind of simply go over a description of how those fossil fuel resources got there. They're fossilized fuels, so they're all of the organic matter, hydrocarbons present from once living things like plants and algae and plankton that were drifting in these shallow seas millions and millions of years ago. They died, they sank to the bottom of that ocean sediment, and then over that millions of years, millions of tons of sediment all accumulated on top of those hydrocarbons, the carbon remains of those once living organisms. And we had these great conditions of time, for sure, millions of years, hundreds of millions of years, and heat and pressure, and different locations on the planet had kind of different heat and pressure conditions. That means that I had different kinds of fossil fuels formed in different places, and that determines if I had coal, oil, or natural gas. We don't need to dig into these two maps into a whole lot of interpretation. I just want us to make sure we can see some type of pattern of where these fossil fuels are located. So the top map here is showing me major coal deposits around the world. The bottom map is showing me major oil and gas deposits, and I can see that there's definitely a pattern that fossil fuels tend to be located in kind of the same areas, and there are some areas that have a wealth of fossil fuels and some areas that have little to no fossil fuels. So let's just take one quick little check in here on that idea of how the geologic processes of time and heat and pressure determine the location of fossil fuels. During the Cretaceous period of Earth's geologic history, Montana was covered with lowland swamps. The plants were buried and slowly decomposed. Which of the following resources would most likely be mined from the plant remains buried in eastern Montana during the Cretaceous period? And the answer is fossil fuels such as coal. Yay! So let's take that idea of how long these fossil fuel resources took to form and review the idea of renewable versus non-renewable. I think it's a pretty easy concept. So I'm going to have you determine if the following statement that I'm going to show you in just a second is an accurate description of the difference between renewable and non-renewable, and justify your claim. Renewable resources are those that cannot be used again and again, whereas non-renewable resources can be reused. So think about that one for a minute. Is that accurate or inaccurate? And justify your statement. So the key word in this description here is really this idea of being used or reused. I would say that it's an inaccurate description. Look at the terms, the vocabulary that I want to have on my note sheet to describe a renewable resource. It can be replenished or resupplied or replaced or reformed naturally at a rate at or near the rate of consumption. So remember, we talked about sustainable use of forests and wood as a fuel. We'll look at wood again here in a minute. That is a renewable resource. I can't use the wood again. Once I burn it as a source of energy, I don't have that same energy source, all of that cellulose and those hydrocarbons that I can burn to release energy, but I can grow more trees. Whereas a non-renewable resource, the key term here to describe this, these are present in a fixed amount. The processes that created them require very long time and those conditions of heat and pressure that once they're gone, they're gone. They are present in a finite or a fixed amount. Let's dig in a little bit deeper to non-renewable resources as we relate it to our big idea on energy transfer. So here's a model that shows the equation, the balanced equation for the combustion of methane. Methane is a fossil fuel. We're going to look at natural gas. That's the main component of natural gas. We'll look at that in a couple of minutes. But I can see from the balanced equation that the same number of carbon, hydrogen, and oxygen atoms exist on the reactant and the product side. After I combust that fuel, I still have the atoms. Those atoms can be reused, you might say, because I can take that carbon dioxide and a plant can take it up in photosynthesis. But I'm never going to have more methane to burn. I'm never going to have the conditions on a human timescale that can put those atoms of carbon and hydrogen back together as a fossil fuel that I can extract and burn because of the conditions that created that methane to begin with. So as I convert that methane into different kinds of compounds, even though the atoms don't disappear, the amount of usable or high quality energy is diminished. I want to take a minute and talk about the equation itself. And one of our big concerns about using fossil fuels is the disruption of the carbon cycle. We take these fossil fuels that are carbon stored in massive amounts that's been down underneath the ground for hundreds of millions of years, and we are extracting them and burning them and putting that carbon as a form of carbon dioxide into the atmosphere. Carbon dioxide is a greenhouse gas. There's no complementary process that takes that carbon out of the atmosphere at the rate that we're putting it into burning fossil fuels. It's true that photosynthesis removes carbon dioxide, but the process of photosynthesis and cellular respiration are in a balance, are in an equilibrium. We keep adding more and more and more carbon through the combustion of fossil fuels that normally would be carbon that would be in the atmosphere. What about renewable resources then? Do we still have the law of conservation of matter here? Well, in photosynthesis, this is an energy process. I can take atoms of molecules of carbon dioxide, combine them with water, and form sugar and oxygen. The difference is that I'm going to continue to recycle those atoms of carbon. The sun comes up every day, and I can do this process of photosynthesis again. So the carbon dioxide that I took out that was converted into a sugar is going to be eaten by an animal. That animal is going to do cellular respiration and put that same carbon dioxide back in the atmosphere. Photosynthesis and the reverse of it, cellular respiration, keep that concentration of carbon dioxide in an equilibrium. We're going to look at biomass fuels and come back to this idea in another section on energy. So we've established that there's this uneven distribution of fossil fuel resources. The geologic processes that created them mean some areas of the world have a lot, some of the areas of the world have none. Well, we can see patterns of consumption as well. This map is showing me color-coded, the light colors, yellow and orange, all the way up to the dark red. That's the amount of energy that different regions use. And I can see a pattern emerge where it appears as the developing countries don't use nearly as much energy as a developed country does. And that makes sense if we connect this to the idea of the demographic transition model and what happens as a country goes through the process of being industrialized. Let's take a look then at a question that there's often a misconception about this when we see questions about per capita energy use on the national exam. So I want you to see if you can describe and compare total resource use per capita between developed and developing countries. I'll give you a minute to think about that one. So one of the biggest misconceptions students have, and it's pretty clear when we read the way they respond to a per capita question, is that a student might say something like, well, countries that have really big populations have a greater per capita energy use. Per capita means per person. It has absolutely nothing to do with how many people there are in a country. I can have a country with a very small population overall, but a very high per capita resource use. So the first thing they wanted us to do here is describe and compare, come right out and make a statement of claim that developed countries have used a greater amount of resources per capita than a less developed or a developing country. And then 2 points for comparing them. And I could do one or the other. So I could say, well, developed countries have a higher standard of living. They have a high gross national product. They have have more money to spend on luxury items, which require a greater use of energy. You could even have stated actual statistical values about how the population of countries is kind of split 20-80. 20% of people live in developed countries, 80% in developing, yet the resource use is flipped. 20% of the population uses 80% of the resources, therefore the per capita, the energy used per person is much greater. Notice you could also talk about the type of energy used. We tend to use fossil fuels in the developed world, whereas in the developing world, they use biomass or a more low-tech fuel. And that'll make more sense when we review the process of extraction that is required to get a lot of the fossil fuels that we use. This is a graph that is showing me global fossil fuel consumption. You would probably recognize that if I went back before the Industrial Revolution, wood or biomass would have been the major source of energy. This is then from the Industrial Revolution on, the number of terawatt hours is a measure of energy consumption. And we can see that after wood, coal came on the scene and really fueled the Industrial Revolution. Coal was replaced primarily by crude oil, which more recently has largely been replaced by natural gas. But the bottom line is that as a country becomes more industrialized, their demand for energy increases. Their total demand and their per capita demand both go up. And the majority of that energy to fuel the industrialization of many of those less developed countries is going to come primarily from fossil fuels. That's concerning to all of us because of the implications of the amount of carbon dioxide being added. So we've been talking a lot about all these fossil fuels we're using, and we're using more coal, more oil, more natural gas. What determines which natural resources we use for energy? What the factors go into that? Well, the first is availability. How much of that resource is there? Where is it located? Is it easy to get? Do I have to build an offshore oil platform that's a couple hours flight from the mainland? Or can I erect an oil well and pump oil right out of the ground? Can I put up a windmill and get kind of energy just by letting the wind turn a turbine? The availability and how easy it is to extract and process and transport is a big factor in our energy decisions. Government regulation also plays a big role. The government can either incentivize or disincentivize the use of certain fuels or our rate of consumption, and they do that largely through taxation. We're going to come back to that in a second. Remember that idea of full cost pricing? If I want to disincentivize the use of fossil fuels, which have all these negative costs associated with them, I could increase the price of that by taxing those fossil fuels that have all the negative problems associated with them. There's fossil fuel subsidies. You may have heard of subsidies in a number of different applications, but certainly some of the biggest subsidies are for the fossil fuel industry. A subsidy is some type of government action that lowers the cost of energy production from fossil fuels. It could be a tax incentive. It could be funding for research and development to build that offshore oil platform and find new sources of oil on the ocean floor. Maybe it's simply saying, here is federal land that belongs to all of us. We're going to let fossil fuel companies go onto that federal land and extract those resources maybe for nothing or for a very low cost. All of these factors determine the price of a certain fuel, and price determines to a large extent our energy decisions. I want to take a minute and clear up another misconception that we often see in the writing of free response. When a student has to ask about a solution or a strategy to reduce the use of fossil fuels, they might say something like, well, the government can raise the price of gasoline and then people won't use as much gas and we won't have as many problems with combustion of gasoline. People will use less. Understand that the government does not set the price of that fuel. The price is determined by the market. Right now, gas is about as low as it could possibly get. That's because with the pandemic and industry shutting down, there's just not a market for all of that oil. So there's a lot of oil on the market. They didn't even have a place to store that oil anymore. So they have to let it go at a really cheap price. The government does not determine the price of oil. The government can determine the price that I pay at the gas pump by heavily taxing or not heavily taxing what I pay for gasoline. All countries are buying oil on a global market. The difference is some states or some countries may want to reduce the use of fossil fuels and apply a heavy tax. Likewise, some states or countries might want people using a lot of that energy and would have a low tax on it. Let's take just a step back for a minute and look at a couple different types of fuel before we go into the detail on fossil fuels specifically. And we talked a little bit about fuel wood already when we were talking about forestry, and I mentioned charcoal. I think I may have shown you that same picture. These terms, fuel wood or charcoal, kind of all mean the same thing. It's a source of energy that is used for people in much of the developing world. It's often the only source of domestic energy they have for cooking or heating or boiling their water. But there's a lot of negative consequences associated with this process, especially when those fires are burned indoors or in a very poorly ventilated area. We're going to come back in the latter part of the week when we look at air pollution, and we'll talk about that as well. One of the solutions that some nonprofit groups are working with people in developing countries to try to provide them with a chimney or some type of ventilation system so that they can reduce the exposure to women and children to some of those indoor air pollutants. So we'll wrap back around to that in a little bit. In general, wood can be used in a developed country as well, probably more in rural parts of the country where people might actually have an outdoor wood burning furnace, not just a fireplace in their living room. This might be the only source of heat for some people, but they can put big logs, a sustainable source of fuel, into that, and then that heat is piped into their home. You may have heard of a wood pellet. This is a picture of a wood pellet stove, and it's indoors, but again, it's got a chimney and it's vented. And it's kind of a great use of many of the waste products associated with logging. I can take even sawdust from construction and I can compact it. It looks kind of like little animal poop or rabbit poop, like little rabbit pellets, but I just buy it in big bags and I put that in my furnace and light it on fire. We can also make those pellets out of things like palm kernel shells or coconut branches, anything discarded during that logging process. And again, if we can start transitioning the developing world to some sustainable uses of a renewable fuel like this, that's really our goal as they start to get more developed and use more energy. So what about those fossil fuels? Let's start off with coal. You probably remember hearing about anthracite, bituminous or bituminous coal, and anthracite, bituminous, lignite, and peat. Peat really isn't a form of coal. It's this deep brown kind of soil deposit that's partially decomposed vegetable matter, and it forms in wet, often very acidic environments, conditions like we would see on a bog. I think these are a couple of guys, little dogs watching them here in Ireland, and they're digging out that peat. That peat will then be taken back and burned, could be in open fire or in more of an enclosed vented fire. We often dry that peat and sell it in a gardening center like peat moss. Remember that this anthracite is the most desirable form of coal. Back to that idea that all these fossil fuels formed under conditions of time and heat and pressure, but what form of coal I have depends on those geologic conditions. It's the most desirable because it has the highest heat content, lowest sulfur content. Remember, coal's got a lot of sulfur impurities that could lead to the formation of acid rain, but it's also in limited supply. I just so happens that this past weekend was up in northern Wisconsin walking along a bog, and it's pretty early in the year for us, but this is kind of what that peat moss, this is what that mossy substance looks like. And then I figured since those guys were digging out that peat moss with their dog, my dog better be in a picture. So what about coal? You guys have a pretty good feel for that peat. Peat would maybe eventually become coal if we gave enough time and heat and pressure. But coal is really what we extract. The main use of coal, as you probably remember, is for generating electricity. And I'm guessing guessing that your teacher got this kind of little mantra down for you about how we generate electricity from any combustion process. This coal is pulverized to increase the surface area. So I chop that coal up, I put it in a big furnace, I heat water, I make steam. That steam turns a turbine, and that is connected to a generator that transmits that electricity out through the grid. That's a lot of conversion. So remember the second law of thermodynamics. I'm going from chemical energy, the potential energy stored in the chemical bonds of that hydrocarbon, to heat energy, to mechanical energy, spinning that turbine, to electrical energy. All of those conversions mean that at each conversion step, there's a loss of quality energy. I just have a lot of wasted energy. And so the more energy conversion steps I have, the less efficient my energy conversion process is. And that's really a drawback. There's a lot of good things about coal. There's a lot of coal. Remember why we use an energy resource. There's a lot of coal. It's really cheap. It's pretty easy to get out of the ground with dynamite and a lot of big trucks. And this process is, I mean, it's on a super large scale, but I'm just really taking this hunk of hydrocarbons and burning them. So it's pretty low tech, pretty easy, pretty cheap, and really vast supplies of coal. Remember that map. We don't even look for new coal deposits because there's so much that we know about that it's hundreds and hundreds of years, but it releases a lot of carbon dioxide when we burn it. One of the ways we can kind of get around that inefficiency of this process with all these energy conversions is the idea of cogeneration. This is just really maybe something you could use as a good solution. It's the idea that if I'm burning that coal and using all that heat to heat water to make steam to turn a turbine, that I can capture all of that excess heat and use it to heat my building. Cogenerate. I'm using the energy that I've generated in kind of a dual way. So our next fossil fuel is natural gas. Natural gas is defined as the cleanest burning fossil fuel with a big asterisk by it, and we'll come back to that asterisk in a minute. Natural gas is, this kind of looks like that picture that we looked at the very beginning. It's a fossil fuel. It's usually found in a layer above oil because it's a gas, it's lighter. The natural gas itself is a mixture, but for our purposes, we can call methane and natural gas the same thing. I could say natural gas, methane, or CH4 if I were writing about this fossil fuel in an FRQ. I just want to point out, I don't need to know this. I don't need to know a lot of nitty gritty about the geology here. I just want to, in order to understand the big problems associated with extracting natural gas, I just have to understand that this natural gas is capped by this impervious layer. If you want to remember that it's a shale cap, that's awesome. Just so you get the idea that it's sort of trapped under this dense shale that's not going to let it through. That's not going to let it escape. So I have a layer of oil and I have a layer of natural gas. Remember that graph that showed us from wood to coal to oil to natural gas? For a while, when we first discovered oil, we knew that gas was there, but we didn't really have much use for it. We didn't have the technology to pressurize it and transport it and burn it efficiently. So as we figured that out, natural gas use is really on the rise. Why? Same thing that drives all of our energy decisions. It's very useful. Most of us may have a natural gas furnace for heating our home. There's a lot of it. We have good supplies. We have good domestic supplies. The cost of it right now is cheaper than coal. We hear a lot of talking points about why we're not using coal and coal miners aren't at work. Remember that our energy decisions are based on cost, and right now natural gas is pretty easy to extract and it's cheaper per unit than coal. The reason we say natural gas is the cleanest burning fossil fuel is that it has less carbon dioxide emissions than other fossil fuels, less sulfur, less particulates. So relative to other fossil fuels, it's clean, but that's that big red asterisk. It's still a fossil fuel. We've looked at natural gas as a transition fuel to get us from fossil fuels into a more sustainable energy future. We still, even though it doesn't have as much CO2, it's still, when I combust the methane, when we look at that balanced equation, I still emit carbon dioxide when I combust a hydrocarbon. You probably remember hearing about hydraulic fracturing or fracking. This is the process to get the gas out of that, free it up because we got that really dense impervious cap rock layer. And that's, again, even if you don't remember the name of it, I just want you to understand that in order to understand why we frack, you got to understand that there's that impervious layer. This process of hydraulic fracturing produces large quantities of hazardous waste. And in addition to that, the methane, once I free it up through hydraulic fracturing, can now enter the atmosphere or the surrounding groundwater. And this is an image of a large hydraulic fracking operation in a northern forest. Understand that I can put a fracking well like this up anywhere. I could be driving in Denver, Colorado and see in an urban area one fracking well. So although I can have big facilities like this, I can have small dispersed facilities as well. So let's go into a little bit more detail in review of that process of fracking so that you can clearly describe some of the problems associated with it and maybe help us come up with some solutions. So the idea here is that I have this fracking fluid. It's a mix of water, sand, and chemicals that I pump down into the well. It's called hydraulic fracturing because that fracking fluid of water, sand, and chemicals is put under really high pressure. I have to crack that impervious rock layer in order to free up that methane. And they use this term propans here. That's the sand. Interestingly, we don't have methane or natural gas in Wisconsin, but we do have a lot of sand and gravel mining, and we have fracked sand mining. We have a lot of sand that the fracking industry likes because of the nice grain size of it. So this propans is the sand. And once I put that in there under really high pressure and I fracture that rock, the purpose of the sand is just kind of hold those fractures open and let that methane seep up. And theoretically, all of that methane is captured by this well. However, in the process of fracturing that rock and allowing that methane to flow, some of that methane is going to get into the groundwater and contaminate it, or it can just enter the atmosphere. And methane is a greenhouse gas more potent than carbon dioxide. It has a higher global warming potential than carbon dioxide does. So while the fuel, when we burn it, may be a little bit cleaner than coal or oil, that methane fuel itself is escaping and entering the atmosphere. It's a little confusing because we're talking about methane as a greenhouse gas, but remember, it's a fuel in and of itself that I still have to then burn. And anytime I combust any hydrocarbon, I'm going to release carbon dioxide. The chemicals are the really big concern here. Notice that my diagram simply identifies it as various chemicals. The fracking industry has not been required to divulge much of the many of the ingredients. We know that there are persistent organic pollutants that are contained within some of that fracking fluid. The people that are exposed to some of those chemicals aren't really sure the exact nature of them. We have that contamination. We also use a great amount of water in that fracking fluid. And what happens then to all of that waste product is that it is stored in these toxic ponds. You may remember hearing about those, and we're going to come back and look at those waste ponds in a little bit as we look at another source of fuel. Let's just do a quick check-in here on the process of hydraulic fracturing or fracking. So we have a couple of different environmental problems there, and then a step in the nitrogen cycle just to throw you for a loop. And obviously the biggest concern here is groundwater contamination. Because if I were going to turn this into an FRQ prompt and I had to describe an environmental problem associated with fracking, I could talk about groundwater contamination. That's just identifying a problem. To describe it, I have to say how the groundwater is becoming contaminated. And remember, the methane can escape and contaminate the groundwater, or those big tailings ponds where all that waste is stored could leak if they're not lined and contaminate the groundwater. The next fossil fuel that we're going to look at are tar sands. And if natural gas is the cleanest fossil fuel, tar sands are the dirtiest fossil fuel. And in fact, that makes them pretty much the dirtiest fuel, doesn't it? So here's a picture of, and I'll show you this on a map in a minute. This is a picture of the area of old growth boreal forest. You know what the boreal forest is because you reviewed that biome in Alberta, Canada, in northwestern Canada, where where these big deposits of oil sand are found. And this is what that area looks like after a tar sand project has come in. Obviously, the first thing that happened was large scale clear cutting of old growth boreal forest, hundreds of thousands of hectares of old growth boreal forest. The magnitude and scale of this destruction is almost hard for our human brain to kind of wrap around and visualize. And I think part of the problem is that this is happening in such a remote area of northern Canada that if you were an APES student, it may not be on your radar. So let's dig in a little bit more about what these tar sands are all about. It's a mixture of sand, clay, water, and a thick, viscous, kind of like molassesy sort of substance called bitumen, kind of like that coal. And it's mined. So if you remember, after I remove all the overburden, let's say I was going to do copper mining or gold mining, surface mining. After I remove all of the trees and all of the soil and I take big equipment and dig down into that sand, this is kind of what that tar sand looks like. And I need to use chemicals and water to process and get the hydrocarbon out of that sand mixture. So the tailings ponds that are created, remember we can have tailings ponds from the tailings from mineral mining, from mining of metallic minerals like copper, all of that waste rock. I can have tailing ponds from hydraulic fracturing where I'm storing all of that toxic fluid, all of that fracking fluid, and I can have tailing ponds from the process of extracting and getting the hydrocarbons out of tar sand. And I'll just try to give you a minute to kind of orient yourself to this image from 1984 and 2011 up in Alberta, Canada, where these tailings ponds are located. So again, this image is just kind of the scale. It's in a little bit closer. And then I took an image just yesterday, so I'm going to show you that one. Again, I don't think we can even wrap our brains around how vast the destruction is of the forest and the massive nature of these tailings ponds. They are now holding 1 trillion liters of toxic waste. And that waste contains a lot of different heavy metals that can biomagnify in the food chain. So many of the indigenous people that rely on fish, for example, or caribou in their diet are getting very high concentrations of these heavy metals from contamination of their water supply by these tailings ponds. This is a Google Earth image that I took just yesterday. So just to orient ourselves, this part right here of the current Google Earth image is this area that you're looking at. I think you can kind of see how that matches up. So since 2011, we have doubled the production of that, and all of these are massive tailings ponds. This is what one of those tailings ponds looks like, and this is a highway with trucks that are bringing all of that waste to those tailings ponds. So it's something that should be of concern to us as we look at how energy decisions are made and the choices that we make and what kind of influence we can have on those. Let's take a look at, walk you through a guided practice question as we look at the idea of a pipeline for transporting oil. You may have heard of the Keystone Pipeline. We have the original Keystone Pipeline, and we're going to in a minute talk about why we would have to transport that oil. Oh, here's where the Alberta tar sands are in this big area up here. So again, the vast nature of them, it's really hard for us to visualize because this is such a remote area of just pure pristine boreal forest, not a lot of development. So the reason I would want to transport that oil via pipeline is to get it to a refinery. We're going to look at refineries and review that in a minute. But you may have heard of the controversy. And I think in terms of pipelines, there's kind of two reasons that people have a problem with the pipeline. Number one, it's the pipeline itself, that I'm transporting oil underground. I think most of that pipeline is buried, but this is going right above the Ogallala Aquifer. That is the major source of water for both municipal, agriculture, and industrial use for a large part of our country. A lot of the pipeline would go through private land, and there are people that may not want a pipeline transporting oil below their land. Maybe it will impact the value of their land, and the company maybe doesn't have a very good track record of leaks or breaks in that pipeline, and the ability to get to that pipeline and quickly repair it as all of that oil is leaking out onto somebody's land. I think one of the other big concerns about the pipeline in respect to the tar sand oil is that people feel that if the pipeline is built, it commits us to using the dirtiest fuel on the planet. That oil isn't going anywhere. If at some point in the future we are so desperate for oil that we need to extract that, it's always going to be there. So I'm going to give you a second to relate this to that beautiful boreal forest and tundra ecosystem that we were looking at, because whether I'm talking about the Keystone Pipeline to transport tar sand oil or a pipeline that's going to transport oil from the Arctic National Wildlife Refuge, much of this oil exists in these fragile ecosystems of the tundra. So I'm going to give you a second to take a look at this question and see if you can describe two characteristics of Arctic tundra that make it fragile and explain how those make it susceptible to damage. As we look at the responses here, they've divided them up into kind of biological, climate-related, and physical. And I think one of the big ideas is that all chemical reactions happen slower in cold, dry conditions. So just the nature of this tundra environment means that rates of decomposition and recovery are very slow. The ecosystem is fragile because it's going to take a long time to repair itself if there's any damage to it. It talks about the permafrost and that soil being very shallow and nutrient poor, and again, the long amount of time it would take for it to recover if there were oil that presented that damage to the ecosystem. Next, let's take a look at tar sands in terms of other problems. The old-growth boreal forest is being removed on a massive scale. Describe two environmental consequences other than those related to boreal forest habitat loss that result from the extraction of bitumen or the transportation of synthetic oil to customers. I'll give you a minute to look at this one as well. Two environmental consequences other than loss of boreal forest could be the extraction or the transport of that synthetic oil. Well, hopefully a couple of the things that you talked about were release of things like NOx and SOx and particulates. We're going to review those in air pollution later in the week. All of the mining waste that has to be stored, those toxic tailing ponds, the ability of that oil to spill or leak during transport through a pipeline, contamination of surface or groundwater. Here they talked about habitat fragmentation from the pipeline. So it wasn't the clear cut to get at the oil sands to begin with, the tar sands to begin with, but the idea that there's even habitat destruction in the construction of the pipeline. So lots of different potential consequences because tar sands are the dirtiest fuel on the planet. So remember I said that we had to transport that tar sand oil down to the Gulf of Mexico region, which is where the refineries are located. So the next concept that we're going to take a look at is what I do with oil to make it into a useful product, because we don't use crude oil in and of itself for anything. We first have to refine it, purify it. It's called fractional distillation or just distillation. And it's based on the fact that all of these different components mixed in that black ugly crude oil, they all have different boiling points. So I have things that are gases at room temperature, liquids at room temperature, thick liquids. And then I get down to things that are actually solids at room temperature that have very high boiling points. And a couple of things I want to point out here. One of the most desirable fractions or components of this mixture of crude oil are these kind of low to medium length hydrocarbon chains like octane, the major component of gasoline. Petroleum engineers might take some slightly longer hydrocarbons and modify them in order to make them the right components for the gasoline, for the fuel I put in my vehicle. So I have jet fuel, I have diesel fuel, I have paraffin wax, I get petrochemicals. That's another big component of this. All of these these carbons that I use to make synthetic compounds that include everything from pesticides to plastics to pharmaceuticals. Anytime I make a synthetic fiber, my dress here is a synthetic fiber. This is a rayon. This is a polyester that's made from crude oil. But they fraction it off into these separate components and then turn that into these synthetic fibers. So we have a lot of different compounds from crude oil, but I have to transport that to a refinery, and they're always located near a big source of water because guess what? We need a lot of water to purify or refine that oil. Let's do a little check for understanding here. Which of the following scenarios is an example of cogeneration? I almost said coevolution. Cogeneration. Got a couple of different things there that look at energy that if you didn't know could look like a reasonable term. Remember, it's using that sort of waste heat from the steam to actually heat a building. Extraction of natural gas by fracking is most likely to result in which of the following environmental problems? That's just kind of groundwater contamination. And that wraps it up for our first lecture on energy. So let's kind of take a look at what all we covered today. We looked at the difference between renewable and non-renewable energy resources. Make sure to have some good descriptive terms in your notes for that. We looked at how energy resources are evenly distributed between developed and developing countries, either the distribution or the use of them. The distribution is determined by geologic processes. The use is determined, how much we use per capita is determined by how industrialized we are, how affluent we are. We looked at all of these different fuel resources from wood to peat to coal, natural gas, crude oil, and the idea of cogeneration. And then we looked specifically at fossil fuels, at some characteristics of them. Remember, we reviewed that combustion reaction. We looked at the process of heating water to make steam to turn a turbine and generate electricity. And we looked at the various methods by which we extract fossil fuels, including hydraulic fracturing. And I think we really focused on these skills, describe patterns of energy consumption, explain why certain resources are located where they are, and justify the use of resources based on ecological, human health, and economic factors. So here is the reminder of the task verbs that you're going to see on your exam, all except calculate. You will not be required to calculate on the exam. And here's your homework that has to do with natural gas from rock and hydraulic fracturing in the Marcellus Shale region of the eastern United States. So you're going to do that for homework and check it with Dr. Sowell tomorrow, where you're going to talk about renewable sources of energy. So thanks for watching. Remember to, as you're going through and answering questions, keep in mind how you're organizing your notes and how they're going to benefit you on your national exam. Good to see you guys. Have a great day. Catch you next time.
Hello, AP Environmental Science students. Welcome back to another review virtual lesson. My name is Dr. Sowell, and I teach APES down in Jacksonville, Florida at Darnell-Cookman Middle High School. All right, so just a quick reminder of our exam date and times, and then remember you can easily find the descriptions of the 2 FRQs on this year's exam. Remember, only 2 FRQs, no multiple choice. All right, so let's start with our warm-up, which is our homework from last night's session, our last session with Ms. Fassler. She talked about energy and looked at some fossil fuel usage and mining. So we're going to start with this question about fracking, hydraulic fracturing. So there's a little article about natural gas from rock, and then A, B, C, and D. So let's look at A. A says, identify and describe 2 water-related environmental problems associated with fracking. So we're looking at an identify and a describe. So there's 2 points for each of the 2 problems that you find. So the first one you could have put is something about the groundwater. So the chemicals or the waste from the fracking process leaking into the groundwater, or some of the actual natural gas methane itself leaking into the groundwater. Or you could put the same or similar issues with surface water, some of those contamination of the wastewater getting into streams or lakes or ponds. And then finally, you could put just the amount of water used. That's a lot of water that is being used during the fracking process. So we could kind of look at unsustainable over withdrawal use of aquifers there. So all water related, groundwater, surface water, just too much. And that's worth 4 points, 2 for each of the identifies and 2 for the descriptions. All right, B, natural gas is considered to be a better fossil fuel for the environment than coal is. Discuss 2 environmental benefits of using natural gas as a fuel compared to using coal. So we're not looking for 2 environmental benefits in general. We're looking at 2 environmental benefits as compared to coal. And you could have said fewer SOx, NOx, mercury, carbon dioxide, those things that are emitted when you burn coal. Or you could have talked about the fact that the mining practices are less destructive. So mountaintop removal is clearly much more destructive to the habitat and into the environment than fracking is. Or you could have talked about soot, that particulate matter, or greenhouse gases, carbon dioxide. Here's an important part to this one. It says in part B, some students did not fully describe the benefits of natural gas as compared with coal. For example, students said that natural gas emits fewer air pollutants than coal without identifying the specific pollutant. This is the commentary that some of the teachers and the readers provide after they've read the thousands and thousands of responses. So the advice to teachers based on these problems was remind students to provide specific information in their answers. Generalities like air pollution or pollution do not demonstrate the level of understanding expected of a student who has completed a college level course in environmental science. At this level, students should be able to specify types of pollutants like SOx, NOx, particulates, mercury, things like that. So again, remember, when someone is grading your FRQs, it's not what you meant that gets graded, it's what you wrote. So write like you've taken the course, be specific. C says, describe 2 environmental drawbacks not related to water use of using the fracking process to extract natural gas from shale. So any environmental drawback of fracking that's not related to water use. Always watch out for these clauses, because when we do grade the FRQs, a lot of times students will miss this, and we'll see them talking about the kind of other than clause in the middle of the question. So you could put something about habitat fragmentation from the drilling site, an increase in earthquakes, methane leaks into the atmosphere, causing an increase in greenhouse gases. All of the machines and tractors and drilling equipment that burn fossil fuels would release SOx, NOx, carbon dioxide, and all of that stuff into the air. Noise pollution, that's kind of cool. And noise pollution from all of the drilling and the truck traffic. So lots of environmental consequences of fracking that are not related to water. And D says, describe 1 economic benefit to society of using fracking to extract natural gas from shale. So you could put, we don't have to rely on foreign sources of oil, so the foreign influences don't affect our price as much. Jobs, that's always a good option if it asks for an economic benefit, because a lot of the things we're talking about need to be built and maintained, and that is a source of jobs. And then finally, you could put the individuals who lease their land to fracking companies can make some money there as well. All right, so that was the review from Ms. Fassler. Let's jump into what we're going through today. So our goal today is to discuss more of the renewable energy sources. So we're going to look at solar, hydroelectric, geothermal, hydrogen fuel cell, and wind energy. So this is the order that it goes in the curriculum, but I'm going to go a little bit out of this order. And then several times today, we're also going to focus on the science practice number 1, concept explanation. You know, you will have to do this at some point probably on one of the FRQs, describing something and explaining something. So we'll practice that a few times. So the first thing, before we get into those sources, I just want to talk about electricity generation a little bit. So remember, electricity is a movement of electrons. So if we're going to make some electricity, we got to move some electrons. And one way to do that is with a generator, an electromagnetic generator. And in an electromagnetic generator, we have magnets and coils of wire rotating around each other. And that rotation causes that flow of electrons. So we take that mechanical energy from the rotation and turning that into electrical energy. Well, how do we get this to turn? Well, we typically put a turbine on it. And how do we get the turbine to move? We put something like wind or water or steam on it that will then turn the turbine, that will turn the generator, that will generate electricity. So I put that little picture up here, remind me to show you this. I went into my classroom the other day and got my little handheld generator out of this. So you can see that these are the magnets magnets, and this is the coil of wire that can spin around. So as I spin, you can see that it lights up a little light. So I'm generating electricity. Exciting. Okay, so let's keep a truck in here. So if we look at the various ways to generate electricity, there's quite a few. And so we're going to look at some that are renewable today, and those are in the green boxes. So let's take a look at this first one. So we could spin the turbine with wind, we could spin the turbine with steam, or we could spin the turbine with water. Either one of these moving things, the moving wind, the moving steam, the moving water, can spin the turbine, which will rotate the generator, which will make electricity. We could also look at the two different ways to spin with water. So we could use a hydroelectric dam, or we can use the movement of tides and waves to spin the water, or to move the water. We could also burn stuff to make steam. So what do we burn? We could burn fossil fuels, coal, oil, and natural gas that you talked about with Ms. Bassler last time, or you can burn biomass, things like wood or charcoal or biogas. Anything that's burning can be used to boil water to make steam. We can also use nuclear fission. Ms. Bassler will be talking about that next. So that fission process, creating a lot of heat that can boil the water to make the steam, to turn the turbine, to generate electricity with the generator. We could also do geothermal or concentrating solar thermal. So the ones in the green are the renewable ones that we're going to talk about today. And all of these spin the turbine to rotate the generator to make electricity. However, there's two down here that will make electricity without the use of the turbine or the generator, and that's solar photovoltaic cells and hydrogen fuel cells. So if you remember this screen and be able to, for each one of these energy sources, describe three things, how it works, the pros and the cons. That's the pattern you're going to see as we go through today. Some of these ones that are involved with heat can also be discussed in terms of cogeneration. So a geothermal power plant can have enough heat to generate steam to make electricity, but we could also use some of that heat to heat up buildings or homes nearby. So using one fuel source for multiple things like electricity and heating, that's called cogeneration. So if we look at the overall energy consumption globally, we see a big chunk of coal, big chunk of oil, big chunk of natural gas, some traditional biofuels, and then the renewables are way up here in a much smaller category. So this is overall energy. On the next slide, we're going to look at just how we produce electricity in the United States, and you'll see that crude oil is not represented there because crude oil, what we use that predominantly for is transportation, so making gasoline, and then plastic products, making plastic products out of that crude oil. So now let's look at just in the United States. This is the electricity generated from selected fuels. And so we see coal, nuclear, natural gas, and kind of chunks there with the majority being natural gas. Then 38% are the renewables, and this is in 2050. If we look at 2020 where we are now, it's a lot less. But if we forecast into 2050, we see a much bigger increase in renewables. If we break down that category a little bit more specific, we see solar, wind, geothermal, hydroelectric, and then other category, things like hydrogen fuel cells. So these are the ones that we're going to talk about today, but you can see that their influence are increasing, especially solar. All right, so what do we need to know with wind? We're going to start with wind, and this is going to be the pattern throughout the rest of today, is describe how it works, and then what are the environmental pros and cons of that source. So for wind, we're just going to talk about how we use wind turbines to generate electricity, and then the pros and cons. Wind is probably the easiest to understand because we basically are just spinning this turbine with the energy of the wind. So kinetic energy of the wind translates into mechanical energy in the turbine and the generator, and then that produces electrical energy out the other end. You may have seen small wind turbines, or you may have actually seen a field of wind turbines, like a wind farm, and the movement of the wind simply rotates the turbine, and that rotates the generator. So in terms of pros and cons, the pros is it's a renewable energy source, and it's also a clean source of energy. So at the point of generating electricity, there are no emissions. Cons, yes, there are some risks to birds and bats that might fly into the turbines. This is also specific to a certain location. Certain locations have higher winds than others, and also winds are an intermittent energy source. Sometimes the winds aren't blowing. We also have a con of habitat loss. Now, while the individual footprint of one wind turbine is rather small, the cumulative effect of a large wind farm would be a significant habitat loss. And then there's the aesthetics. Let's just imagine that I bought a house right here with the view of the mountains, and it's gorgeous, and I really love it. And then in a couple of years, someone built this wind farm in between my house and the view that I wanted. So that might kind of, lower my property value, or I just might not get as much aesthetic pleasure from looking at mountains. So we kind of have that NIMBY effect, not in my backyard. All right, so let's switch over to hydroelectric. So we are going to describe how electricity is generated from a hydroelectric dam. We'll look at the environmental impacts of those dams. We'll look at tidal energy, how we make electricity from tides. And so there's really three big categories of using moving water to generate electricity. The first one would be a dam. That's when we build up water behind the dam in a reservoir and then let it flow through to spin the turbine. Another one is just taking a small turbine and putting it directly into a river, a smaller river. And finally, it's using those tides. But all three are using the moving water to spin a turbine, to spin a generator to make electricity. So let's start with the dam. So the dam is this solid kind of concrete wall built into a river, and the water behind is called the reservoir. So the reservoir builds up, and all of that pressure pushes water through the tube called a penstock, and it hits that turbine, which spins the generator, which makes electricity. But the word reservoir is an important vocabulary word to remember about dams because it's often used in explanations about the impacts of dams on the environment. All right, so one of the unique environmental consequences of building a dam is habitat fragmentation. So not just imagine you're a little fish, and all of a sudden you hit this dam, well now your habitat has been fragmented. You can't get to the rest of your habitat. This is particularly important for things like salmon, which spawn upriver. And then also habitat loss from the reservoir. So behind the dam, the water is now flooded what used to be terrestrial land, and that's been a habitat loss for this terrestrial species. Let's go back to the idea of the fish. If I'm a salmon trying to get past the dam, I can't anymore, and therefore I can't spawn, and then the population of salmon will be greatly reduced. So one solution to that is called a salmon ladder. And a salmon ladder is a structure almost like a set of stairs to the side of the dam that water flows down, and the little salmon can jump up the salmon ladder to reach the reservoir. So just an interesting little fact about how you can kind of mitigate the effects of that fragmentation. A famous dam to know, not only do we have the Hoover Dam here in the United States, but the biggest one is the Three Gorges Dam in China on the Yangtze River. It is a huge electric power generation facility. So it's just a famous one that you may hear about. So let's look at some overall pros and cons of these hydroelectric dams. And this is the Hoover Dam, and you can see the built-up reservoir behind it, and then the river below that, much smaller, less volume of water. So some pros: renewable energy source. There's no air pollution during operation. And then this reservoir also has some benefits in terms of economic and recreational benefit for fishing or irrigation. So there's some uses for this built-up water back here. Cons: location specific. You have to have a river big enough and wide enough with enough power to do this. The habitat fragmentation and loss that we mentioned before. It's expensive. Okay, so it's expensive to construct. It may displace humans. So this happened significantly with the Three Gorges dams, because once that was built, the reservoir flooded places where humans had lived before, and those individuals were displaced. A unique environmental consequence of dams is also loss of downstream sediment. So I want you to imagine that the Hoover Dam was not there. As this river flows downward, it carries with it sediment and nutrients, silt that will be deposited downstream and can enrich the soils with greater fertility, or it might deposit into the ocean in terms of like a delta. So that sediment, which would normally flow downstream, is blocked by the dam, and so that has negative consequences downstream. It can also reduce the efficiency of the dam if it silts up too high. It kind of blocks all that water being pushed through the dam. All right, so let's do a quick check for understanding here. So this question says the Colorado River runs 1,450 miles from the headwaters of the Rocky Mountains to the Belleville, California. The river has many dams, aqueducts, and canals that divert water in order to supply water for electricity, irrigation, recreation, and domestic use. The question says, describe and discuss 2 environmental problems that are associated with water diversion. So let's take a look at this A first. So again, describe and discuss. There's 2 parts to this. So let's take a look at this person's response. One particular consequence of diversion is, such as in the case of the Hoover Dam, the prevalence of siltation upstream and the filling of the river with sediment which would otherwise be washed downstream. Eventually, it is believed water levels will be decreased upstream to such a point that both the hydroelectric power and the upstream freshwater ecosystem of Lake Mead will be greatly impeded. So there's a point right there, talking about that siltation that is going to affect what gets washed downstream. And then the person continues to say, water diversion also alters the lives of many organisms in the river ecosystem, such as spawning fish, which periodically travel upstream to lay their eggs of the next generation. Dams make such attempts to reproduce impossible. So there's 2 points there. So this one gets the description, this one gets the description and the discussion. All right, so here is the overall rubric. So talking about that loss of water volume or sediments downstream, or other ones that talk about the increase of water in the reservoir, things like flooding behind the reservoir. So again, points for description and points for discussion. All right, now let's go to tidal energy. Tidal energy is almost like an underwater wind turbine. So we're still extracting power from moving water. We're just doing it under the water as opposed to in a dam. And it benefits from these daily regular cycles of tides, but not all tides are equal. The tide here in Jacksonville, where I live, may be very different from the tide off the California coast or in another country. And clearly, we're not going to be using this in the middle of the United States, not around a coast. So let's take a look at a little video clip that talks about some of the details of tidal power.
Tidal power. Tidal power is a form of hydropower that converts the energy from the natural rise and fall of the tides into electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth. Tidal plants can only be installed along coastlines. Coastlines often experience 2 high tides and 2 low tides on a daily basis. The difference in water levels must be at least 5 meters high to produce electricity. Tidal electricity can be created from several technologies, the main ones being tidal barrages, tidal fences, and tidal turbines. Tidal barrages are the most efficient tidal energy sources. A tidal barrage is a dam that utilizes the potential energy generated by the change in height between high and low tides. This energy turns a turbine or compresses air, which in turn creates electricity. Tidal fences are turbines that operate like giant turnstiles, whereas tidal turbines are similar to wind turbines, only underwater. In both cases, electricity is generated when the mechanical energy of tidal currents turns turbines connected to a generator. The generator produces electricity. Ocean currents generate relatively more energy than air currents because ocean water is 832 times more dense than air, and therefore applies greater force on the turbines. Tidal power is easy to install and renewable, having no direct greenhouse gas emissions and a low environmental impact. Because the ocean's tidal patterns are well understood, tidal energy is a very predictable energy source, making it highly attractive for electrical grid management. This sets it apart from other renewables that can be more unpredictable. However, adoption of tidal technologies has been slow, and so far the amount of power generated using tidal power plants is very small. This is due largely to the very specific site requirements necessary to produce tidal electricity. Additionally, tide cycles do not always match the daily consumption patterns of electricity, and therefore do not provide sufficient capacity to satisfy demand. That's tidal power.
So this is the next one that I want to show you. It's just a really unique tide. This is the Bay of Fundy in Canada, and it shows a really dramatic, really deep change in low tide versus high tide. In some places like where I live, the tide maybe, I don't know, 20 or 30 feet that comes in, but it really doesn't change depth-wise that much. It just kind of water comes in and water comes out, and it's spread out over a really flat terrain like Florida's coast. Whereas in this particular bay, the structure of the bay really does push the tide up really, really high, and it falls down really, really low. So just imagine the power that be harnessed for tidal electrical generation. So you can see the low tide out there, and then you'll start to see it come in a second, people walking around, and there comes the tide. So that kind of a tide would be common maybe in a lot of beaches, but this all of a sudden becomes really, really, really deep. So all of that water coming in can turn a turbine, and that same volume of water coming out could turn a turbine. So in places like the Bay of Fundy where there's big, big tidal changes, this type of energy would be useful. So let's look at some pros and cons. Clearly, again, it's a renewable energy source. There's no emissions during operation, and it's regular. The tides are going to come and go twice a day, and you can count on them. Cons, like I said before, it's location specific. There's probably some risk to marine species, just like the wind turbines are at risk for birds and bats. And as the little video clip said, the production times may not match the demand times. So where the high and low tides are going, that's when the electricity would be generated. But you may need electricity in between the tides, and that would work very well. Another way to generate electricity from flowing water is to simply put a small turbine and generator directly into flowing water. So as opposed to a dam, these just kind of go right into the water, the turbine spins, and that makes the generator rotate to make electricity. A lot of these are marketed for individuals who camp and hike or outside a lot to charge up small devices. All right, let's do a quick check for understanding about hydroelectric power. So dams are built by humans for various purposes, including hydroelectric power generation and control of downstream flooding. Explain, keyword there, explain how electricity is generated at a hydroelectric dam. So let's look at this person's response. This person said, at a hydroelectric dam, water passes over an impediment, which turns a turbine, which creates electricity. Well, there's 3 points available for this answer, and this individual gets 2 out of it. So they talked about the water moving, the flow of water, spinning a turbine, but then they just leave off the part of how the electricity is created through the generator. So 2 out of 3 points. Let's look at another student response. As the water is allowed to flow through the dam at a controlled rate, the water turns a turbine, which then runs an electric generator, thus producing electricity. So there's all 3 points. So again, if you see the word explain, you need to be sure that there's enough verbiage and detail to really explain what they're asking for. So here's the rubric for that. So there's 3 points of this. 1 point for talking about the movement of the water, 1 point for spinning the turbine, and 1 point for having the generator make electricity. B, for the same question, says identify 2 economic factors other than hydroelectric power generation and control of downstream flooding associated with dams. So this student said the dam provides an area for recreational activities such as fishing and jet skiing, which brings in revenue to that society. People go to the dam and pay to do different water sports, thus helping the economy. Boom, there's a point right there. They really explained what that economic benefit was. The second one says the dam also provides jobs during the construction of the dam and then afterwards the running of the dam, therefore lowering unemployment rates and helping the economy. Boom, there's another economic benefit. So this person gets 2 out of 2 points. Let's look at this one. Dams such as the Hoover Dam are tourist attractions, and tourism generates money for the surrounding businesses. Boom, there's that same point about tourism and recreation. Then they go on to say using water to generate power is also cheaper than having to drill, refine, and transport oil. Well, this only gets 1 out of 2 points because the second thing they talked about, the generation of power, is exactly what the question did not want, other than hydroelectric power generation. So again, be sure when you're reading your questions, read them slowly and carefully, and pay attention to these clauses that may direct your answers to include something other than something else. So here's the possible answers to that. You could have said recreation and tourism, jobs. You could have said using the water for things like irrigation of fields, commercial fisheries, or commercial shipping. All right, so let's shift to solar energy. So to do this, we are going to first describe the difference between active and passive solar energy systems. Then we're going to look at solar photovoltaic cells. Then we'll look at the pros and cons again. All right, so let's start with passive versus active. These are just 2 broad categories that are really easy to distinguish. If you have no mechanical or electrical devices, you're looking it passive. So passive solar energy systems absorb heat directly from the sun without the use of mechanical and electrical equipment, and energy cannot be collected or stored, as opposed to the exact opposite of that, which is active, where we are using mechanical and electrical equipment to collect and store the energy from the sun. All right? So we'll go into each of these and give some examples. So let's do solar or passive solar first. So this is again no mechanical or electrical devices, and this would be something like passive solar heating, types of designs of buildings. So for example, if I want to reduce the amount of heat in my house, maybe I plant a large tree to shade my house to reduce the heat. Or maybe if I want more heat in my house, I build southern facing windows, especially if I'm in the northern hemisphere. So a southern facing window that would collect all of this heat, and then maybe some cement floors down here that will kind of store some of that heat, will radiate the heat back to the house, almost like a greenhouse effect. You're using that idea of heat coming in passively through something. Or you can think about like a solar cooker, using all the sun's energy focused through mirrors all into one little place right here where you can boil water or cook some food. But again, you are not using any mechanical or electrical devices, and you are capturing the heat from the sun. So here's another example of active solar heating now. So it's another example of heating, but now we're going active. So this is an example of a collector on the roof. Please do not confuse this with solar photovoltaic cells. This is not a solar panel that you might be more familiar with. This is almost like a giant mat that sits up on the roof, and inside are all these little oiled pipes that water flows through. And as that water flows through, the heat from the sun will heat up the water. So cold water comes in, runs through all these little pipes on the roof of the house, and it ends up being a lot hotter, and the hot water can be used in the house for different things. Or you might be able to use it to heat a pool, for example. So you might have cold water from your pool going up onto the roof, and then moving through these little pipes, being pumped through, getting hot, and then coming back into the pool. So same system here. The hot water coming to the house can be used for appliances, or you can even transport it through the floor and heat the floor. But again, this is not about generating electricity. This is about actively pumping heat into your house that's been captured from the sun. So now let's make some electricity. So this is another form of active solar. So this is a situation where I have a large tower. So here's our large tower, and at the top there is a liquid. These thousands and thousands of mirrors that are out into this open desert area are all pointed directly at this tower. So each mirror is reflecting sunlight into that one location, and that obviously is going to be a huge temperature increase that can be used to boil a liquid, to generate steam, to turn the turbine, to turn the generator, to make electricity. And also because we're making heat, perhaps we could use some of that heat to heat buildings or do other things with. So it might be a source of cogeneration of electricity and heat. All right, so now let's go with what you're probably more familiar with, solar photovoltaic cells, or just PV or solar PV. This is about light. It's not about heat like the other things. And this is when we have these semiconductors within the panel, and as soon as they're hit by the light, they release the electrons, and those electrons begin to flow, and then we have electricity. And it could be on small scale, like even your solar calculator, or it might be a solar panel on your roof, or it might be a set of solar panels in a big field that's really large scale. But no matter which scale it is, we're not spinning a generator to make electricity. The electricity comes from the semiconductors in there that when light strikes, it moves the electrons around. So let's take a look at solar.
Solar PV. Solar photovoltaic cells, or as it's commonly referred to, solar PV, is a technology that converts the sun's energy into direct current electricity by using semiconductors. When the sun hits the semiconductor within the PV cell, electrons are freed and form an electric current. There are various semiconductor materials, the most mainstream being crystalline silicon, but other materials are being tested to increase the efficiency of converting sunlight into electricity. Unlike solar thermal technologies, solar PV can only use direct sunlight, which means when the sun doesn't shine, electricity isn't produced. One of solar PV's major advantages is that it transitions electricity generation from big, centralized facilities to smaller, decentralized production sites, like the roof of your house. This turns energy consumers into so-called prosumers, people that produce and consume their own electricity. Another advantage is that solar PV utilizes the most abundant renewable resource on Earth. Estimates show that there is 10,000 times more solar energy coming to the Earth's surface than our global annual fossil fuel demand. Traditionally, concerns about solar PV were about cost, intermittency, and efficiency. Large-scale implementation and rapid cost declines have surfaced more complex issues such as grid compatibility, lack of solar industry expertise, and the use of rare and precious metals that make up the cells. That's solar PV.
So let's look at some overall pros and cons. Pros should be pretty evident. It's a renewable energy source, and there's no air pollution or waste during operation. Some of the cons, well, it's an intermittent energy source. If the sun's not shining, there's no electricity. There could be some habitat loss or habitat fragmentation from these large solar fields. And then there's also significant cost involved. This has not yet come down to a point where it's as competitive cost-wise as some of the other electricity generating sources. Then we also have to think about how we're mining and extracting the elements and the materials needed to construct the panels. All right, let's do a quick check for understanding about solar. So this question says, upon receiving notice from their electric utility that customers with solar power systems are permitted to sell excess power back to the utility, an Arizona family is considering the purchase of a photovoltaic solar energy system for their 2,700 square foot suburban home. The initial cost of the systems they are considering range from $7,000 to $3,000. A says, describe one environmental benefit and one environmental cost of photovoltaic. So here's where you just do your pros and cons, but be sure that it's environmental and not economic. So the first person says photovoltaic power systems are environmentally beneficial because they release no harmful pollutants or emissions. Let's stop right there. If the person had stopped right there, they would not have received the point because it's talking about generic pollutants or emissions. But they get the point because they say light, carbon dioxide, sulfur, ozone into the atmosphere. So there's 1.4 benefit. There's no harmful emissions or pollutants. Then they go on to say an environmental cost of photovoltaic system is that they require large amounts of open land to generate ample amounts of energy, and therefore may result in the clearing of a forest or natural habitat. Boom, there's the other point. So the official scoring guide for this, you could talk about any of these environmental benefits that really do contrast them with other energy sources, like there's no nuclear waste like you find at a nuclear power plant, those kind of things. And in terms of the cost, the negative to the environment was a lot about how they were manufactured, that you'd have to use water or other resources to build the solar panels. And then there's issues with the infrastructure for the commercial use of the photovoltaic systems. So yeah, 1 point for environmental benefit, 1 point for cost. D says, I'm jumping around a little bit on this question. D says, describe 2 ways that the homeowners could use passive solar designs and or systems, and for each way, explain how it would reduce the homeowner's energy costs. So there's 2 things you have to do here. You have to describe a passive solar energy design and then explain how it would reduce costs. So let's take a look at a student sample. Homeowners who live in the Southwest can build homes with windows facing the northeast to help keep their homes cool from the sun. This would reduce the homeowner's cooling costs because they wouldn't have the sun blasting its heat into the homes during the hottest time of the day. Good. There's a description of what they would do design-wise to the house, and then the other one coming from how it would lower their costs. Then they go on to say homeowners could lower their thermostats during the winter and wear more layers of clothing to stay warm and reduce energy costs. They would reduce the cost by using the thermostat less and therefore using less energy. While that is true, it gets no points because that's more of a behavior change and not a design or system that they've installed into the house. So again, there's lots of possible solutions here in terms of design elements, in terms of skylights or overhangs or window treatments, but it had to be something that you would design or built into your house, not a behavior. All right, let's switch over to geothermal. Geothermal, again, we're going to describe its use and then the pros and cons. So to do that, we will describe how we generate electricity from geothermal and then look at pros and cons. So same patterns again. So in a nutshell, geothermal power plants are using the heat from the earth, deep inside the earth. So we are drawing up really, really hot water from deep in the ground that we can then use to spin the turbine. That steam spins the turbine that moves the generator, which makes electricity, and then we can re-inject that cooler water down into the ground again. But the source of the heat is not coming from us burning something or the sun or anything. It's coming from inside the earth. Let's take a look at an example of that.
Geothermal wells are drilled into the Earth's crust at approximately a depth of 3 to 10 kilometers. The heat is extracted with a variety of methods, but in most cases is drawn from the earth using water and steam. Hot water
from the earth may be directly extracted to heat homes and buildings. This is done either by directly circulating hot water through buildings or by pumping it through a heat exchanger that transfers the heat to the building. Geothermal heat can also be used to produce electricity in a geothermal power plant. Electricity is generated when geothermal heat produces steam that turns turbines on a generator. The major regions of geothermal development are in the most volcanically and tectonically active regions of the world. Though geothermal energy is currently a small player in the world's energy mix, one of its key advantages is its reliability and consistent power generation, which means it can provide baseload electricity. Concerns with geothermal include the accidental release of CO2 and hydrogen sulfide emissions stored in the Earth's groundwater that is often used to carry geothermal heat to the Earth's surface. Additionally, drawing heat from the Earth's crust can, if done irresponsibly, lower the ground temperature below the surface. The upfront costs for geothermal energy production are relatively high. It is expensive to carry out the seismic sensing, test well drilling, confirmation testing, and other necessary preliminary investigations to ensure that your new geothermal plant will be capable of meeting desired production. That's geothermal.
So just like I said in the little clip, the areas that are most likely to use geothermal energy are those places that are have lots of tectonic or volcanic activity. So we can see here, this is the Ring of Fire, and there's some of the other fault lines. But one of the most unique places is Iceland. Iceland gets almost every bit of electricity from a renewable resource. So about 75% come from hydroelectric dams, and 25% of that is geothermal because they're located right there on that plate boundary. So here's a funny little clip of the benefits of the geothermal power in Iceland.
Hi, I'm Gudrun. Welcome to Iceland Academy. You know, Icelandic nature isn't just amazingly pretty, it's powerful too! Geothermal power makes the land of ice hot and buzzing, since it creates heating for around 9 out of 10 houses, and almost 30% of all our electricity. The other 70% is also created by natural processes, such as water and wind. For over 100 years, we have used this natural power to generate clean energy to heat our homes. And that's why Icelandic homes are so warm in every way. We don't need to brag, but we gave up domestic heating with dirty coals and oil way before it was cool. It's also essential to grow our year-round vegetables in geothermal greenhouses. I mean, you didn't really expect these juicy tomatoes to grow wild right between the dicers and glaciers. The natural power also inspires numerous innovative companies in various fields of work, such as genetics and health-related tourism. The energy even gives us a chance to get up close to wildlife at its biggest. And it's even more special on a silent boat, powered by electricity from renewable sources like waterfalls and hot steam. And last but not least, it warms our geothermal pools. And with great power comes great responsibility. So enjoy it. Scout!
So clearly Iceland is enjoying their geothermal. And not every place in the United States has the same capacity for geothermal energy to be used. You can see that there's more geothermal resources in the western part of our country. So overall, some pros and cons. It's a renewable energy source, clearly. And during normal operations, there's no carbon emissions. It's really reliable and consistent. You know, the Earth is still hot. It's going to be hot. Some of the cons, again, very location specific. Very expensive upfront to construct. And you do have the unintended consequence of some leaking of hydrogen sulfide into the atmosphere. All right, so we're going to end with hydrogen fuel cells. And again, the pattern is, how does it work? Pros and cons. So to get there, we're going to describe how it works. Look at the pros and cons. So as a brief overview, this is what a hydrogen fuel cell looks like. You have an anode and a cathode. And in between, you have an electrolyte membrane. The fuel for hydrogen fuel cell is obviously hydrogen. So you're going to put hydrogen as your fuel into the fuel cell. What's going to happen? This anode is going to split that hydrogen into protons and electrons. It's going to send the protons through the membrane, but it's going to put the electrons on a very different path. And that little circuit that they travel through, that movement of the electrons, there's your electricity generation. And the really brilliant part of hydrogen fuel cell is that the only waste products are a little bit of heat and some water. I mean, that's just brilliant. If we could really tap into hydrogen fuel cells, think about how environmentally sustainable that would be. So let's take a little quick look at their clip.
Hydrogen can also be used for electricity production through a fuel cell. A fuel cell is an electrochemical cell which produces electricity by converting chemical energy into electrical energy. When hydrogen is combined with oxygen in a fuel cell, it produces heat and electricity with only water vapor as a byproduct. Fuel cells are unique in terms of the variety of their potential applications. They can provide energy for systems as large as a utility power station and as small as a laptop computer. Fuel cells can provide electric motor transportation for vehicles and provide power in stationary and portable power applications. Fuel cells have no emissions at the point of operation. The most significant advantage of hydrogen is that it is an efficient energy carrier. However, the ultimate challenge with hydrogen is getting it in its pure form. While some of its applications appear attractive for environmental reasons, deriving hydrogen requires energy that can result in greenhouse gas emissions and air pollutants that lessen the overall environmental benefits of the technology.
So let's just repeat that again. So while the hydrogen fuel cell itself, as a way of generating electricity, is brilliantly clean, the problem becomes, where do we get that hydrogen gas from?
In addition, cost and practicality.
So here's an example of there's some buses in London that run on hydrogen fuel cells, and there's several examples of this around the world at different scales. This is just one that I'm familiar with. But when we look at the pros and cons, again, pros and cons, there's no emissions, it's very efficient. But the cons, like I said before, where do we get this hydrogen gas from? So one way we can produce hydrogen gas is through electrolysis of water, but that requires energy in and of itself to create the hydrogen gas. And then if we're getting the energy to do that from a fossil fuel, well then how clean is this energy source of hydrogen fuel cell? And then we just need some way to distribute this to customers. Just think about how you put gas in your car. There's a gas station everywhere, and there's pipelines and trucks, there's infrastructure to bring that gasoline to you. We don't have that yet for hydrogen. But the biggest part is this: where do we get the hydrogen gas from? We can make it, but a lot of times making it requires us to use fossil fuels to get electricity to make that hydrogen gas. All right, let's do a quick check for understanding. So which of the following is a true statement about passive solar heating? So you should have picked B is part of the kind of related to the greenhouse effect. Remember, passive solar heating is no mechanical or electrical equipment. And again, we're talking about heating, not generating electricity. Let's look at one more. Which of the following energy sources is not derived directly or indirectly from solar energy? So this one might be a little tricky one, but the answer is geothermal. So geothermal obviously is not directly or indirectly related to solar energy. Photovoltaic is, but you may think, well, how is hydroelectric or biomass or wind? Well, yeah, the water cycle is powered by the sun. Biomass, that's living things, photosynthesis, the sun. And then the unequal heating of the earth is causing wind currents. So everything is directly or indirectly related to sun except geothermal. All right, so where did we go today? We talked about solar, hydroelectric, geothermal, hydrogen fuel cell, and wind. And for each one, how does it work? Pros and cons. And then we also practiced several times being able to describe and explain some of these concepts. So again, I love this little diagram. It helps me to remember everything all in one spot about how the different ways we can produce electricity. All right, so your homework for tonight is this question. So this question starts with a graph. And let's just kind of deconstruct the graph a little bit before we leave today. So the first thing you need to do when you see a graph is slow down, look at the pieces of the parts, find out what's going on, and then figure out what story it's trying to tell. I like to start with the axes. So on the y-axis here, it says GDP per capita US dollars. So we're looking at the gross domestic product per capita, per person, right? So we're talking about income here, how much money the average individual person is making. And then if we look at the x-axis, annual electrical energy consumption per capita, kilowatt hours, kWh. Although this year's exam, the 2020 exam, will not have you do calculations, you still need to be able to understand and interpret quantitative data. So while you may not be asked to calculate, kilowatt hours, you still should be familiar with what that unit means and how to understand it in context of a graph or a chart or a table. So we've got electricity consumption here and income here. And then it asks you for a few questions. It's going to ask you to do some description and some explaining. So remember, those two task verbs mean something. They should dictate or influence your writing. I do want to make one modification, though, part D gives you an option of choosing either sugarcane or tar sands. I would like you, for the purpose of homework, to just pick the tar sands, because that's something that Ms. Sassler talked about last time, and she will go over the answers to this next time. So thanks again, apes. Hope you're having a good day. Hope you have a good afternoon, and I'll see you next time. Bye.
Hi, APES students. Welcome back to the AP Environmental Science virtual classroom. I'm Ms. Sassler, and I teach APES in Marshfield, Wisconsin. We're going to start by taking a look at the question that you did on geothermal energy with Dr. Sowell for your homework. I think he went over the kind of the nitty-gritty of what's going on in the graph there, so we're going to jump right into question A. There was a little bit of a sort of a confounding idea here that Iceland's position on the graph, it just looks like they use a lot of energy relative to their GDP. So in the first prompt, you were going to describe how electricity is generated from a geothermal energy source. This task group is asking me to describe a process. So the rubric really was looking for two basic steps in that process. Number one, something that communicated a conversion from thermal to mechanical energy. You certainly didn't need to use those terms. You could have described high pressure hot water pumped out of the earth to then produce steam to turn a turbine. You could talk about wells being drilled and that steam piped directly to turn a turbine, or you could have looked at heat, hot water pumped out of the earth going to a heat exchanger, and that other liquid then creating a vapor that turned a turbine. The second part of the process was some step that communicated you understood that the mechanical energy of turning that turbine was then used to generate electricity. So I think most of you probably got that point. Next, we went on to this contradiction that China's got kind of a low per capita GDP. Each person doesn't make a lot of money. They also have a low per capita energy consumption. Each person individually doesn't use a lot of energy, yet they have the highest CO2 emission of any country. Can you explain that apparent contradiction? And that was that understanding, that idea of per capita that we looked at recently, that even though each individual doesn't use a lot, China is the most populous country on the planet, and the sum of that altogether represents a large consumption. Letter C was going into other problems associated with other emissions from burning other than just carbon dioxide. I'm not going to spend a whole lot of time here because we get into air pollution. After today's lesson, we have 2 days on air pollution. So you can take a look at your answer, but we're going to get into the nitty-gritty of this actually starting tomorrow. So we'll look at that again, those human health impacts. Then we went to tar sands, which we had talked about the day before that. And we again have to describe a process by which fuel is generated from tar sands. And I was looking for 2 points or description of that process. The first one had to have something to do with extraction, that we use surface mining, and many of you maybe talk about the clear cutting the overburden and removing all the soil and then literally digging all that sandy material out through surface mining. And the second point was describing something about the processing of that, how I had to, with either hot water or steam, extract that bitumen from that mixture of sand. Letter DII, to disadvantages of tar sands. The list is quite long. We focused on most of these first ones when we talked about tar sands. It's a non-renewable source. There's a lot of habitat destruction. And I want to spend a minute talking about this concept of low net energy yield. It's this idea that it takes energy to get energy. So all of the energy that went into finding the tar sands, surface mining the tar sands, processing the tar sands, transporting that oil via pipeline to the Gulf of Mexico, refining it, so that by the time my net energy, the amount of energy that's actually left over for me to finally combust or burn to get some use out of, is very low. So how much energy is left after all the energy I expend to get that resource to begin with? I'm guessing based on our discussion, a lot of you also probably focus on those tailings ponds or the storage of waste or the large amounts of water that become contaminated. Finally, you were comparing tar sands to sugarcane and identifying and justifying which was more sustainable. There's only one correct answer you could have chosen in terms of more sustainable, and that's sugarcane. You could not have justified tar sands being more sustainable. Sugarcane is made from a renewable resource. It's not a fossil fuel. It uses new carbon, not old. We're going to clarify that when we look at ethanol from biomass in a little bit. And it don't create that toxic waste from those tailing ponds or that other pile of waste from the mining process. So today we are on day 3 of the energy unit. This is a big unit. We have 3 learning targets left to address, but we spent a lot of time looking at energy. And you probably know, like you did in your class when you first learned about energy. And as we talk about getting notes organized for that open notebook test, really think about pros and cons and solutions, because overall that's really everything we need to be able to know about energy. Being able to describe a process by which we obtain useful energy from different fuel sources, the advantages, disadvantages of that, and some potential solutions. So today we're going to look at nuclear power, energy from biomass, and focusing again on looking at models of a nuclear power plant to understand how they work, looking at different approaches to problems and the pros and cons of them. Remember, we are not doing any calculations. That would normally have been where we would have gone with energy conservation, but we'll focus instead on solutions when we look at energy conservation. Just a reminder that our exam is these 2 free response questions on May 18th over the first 7 units. So we're finishing up 6 energy today, and then we'll have 2 lessons on unit 7 on air pollution. So again, you're really wanting to start focusing in on how that exam day is going to look with the notes and resources that you have that you can use on the exam. There'll be a lot more information about that coming shortly. So let's jump into our review of nuclear power. When we describe an energy source, one of the first characteristics we listed in describing it is simply to say if it's renewable or non-renewable. The raw material for a nuclear reaction to generate electricity from nuclear reactions is uranium. Uranium is a mineral. It's found in the Earth's crust, and I mine it just like I would mine copper or gold or iron ore or whatever the case may be. So it is non-renewable. It is present in a fixed or finite amount. There is, however, a pretty abundant supply of uranium, especially when you compare how much uranium it takes to get energy. We're measuring that on the atomic level. And uranium has naturally occurring isotopes, different forms of the same element that have different masses. And the one we're focusing on is what we call uranium-235. This is the atomic mass of that specific radioisotope. And when I mine that uranium, again, looking at the entire energy cycle, the first step in getting energy from nuclear power is mining uranium. So I have all of the issues associated with mining, surface mining, metallic mineral, and the waste products I create. Then I have to kind of amp up the amount of fissionable material so that I get what is called like a little nuclear pellet. And there's a penny here just as a size comparison. And I load all of those pellets into a fuel rod. So we know that uranium-235 is the raw material. What do I do with that uranium-235? How does that get turned into useful energy? Well, it starts with bombarding an atom of uranium-235 with a neutron. And it fissions, it splits apart, it cracks. And there's kind of 2 things that result from that. Number 1, I get these 3 neutrons that are rejected. Each of those neutrons has a little bit of mass, they don't have any charge. They can in turn hit another atom of uranium-235, which spits out 3 neutrons, which each of those can hit another atom of uranium-235. And that's what we refer to as a chain reaction. This conversion, this splitting of this atom converts a tiny little bit of mass into energy, heat energy. And we're going to capture that heat energy in just a minute. But the other thing we really want to focus on is these fragments. fragments that are created. So yes, I get these neutrons, 3 neutrons that are spit out, but every time I fission an atom of uranium and eject those 3 neutrons, I also create what are called these fission fragments. And that's what we're going to focus on for a little bit. It's if I were going to write the gamma decay reaction, there's gamma radiation emitted. If I were going to write the nuclear equation, which you don't have to do, trust me, what you need to be able to describe is this basic process. But you need to get the conceptual understanding that there are products of the splitting or fissioning of uranium. You don't even need to know what they are. You simply need to be able to describe them as high-level radioactive waste. So let's focus in on that high-level radioactive waste and how we get that, what do we do with that energy. So this is the part of the nuclear power plant that we just looked at. This is the core of the reactor, if you will. This is the other part of the reactor where we're actually going to generate energy. And from here on over, that second part, this doesn't look really any different than a coal-burning power plant or a power plant that's burning waste material. If I combust something, I heat that water, make steam, turn a turbine, connect it to a generator, and create electricity. But when I generate electricity from nuclear power, the energy to heat the water comes from that energy that's released from fissioning the atom. But from there on out, the description is the same. So I fission an atom of uranium, release a little bit of energy, and that heat from that fission heats water, makes steam, turns a turbine, connected to a generator to make electricity. In the core of the reactor, we have what's called a control rod. And these are created of a material that will absorb neutrons. So when they hit, I can put those control rods further down in and slow down my reaction, because when I lower those control rods, instead of those 3 neutrons fissioning other U-235 atoms, they're being absorbed by the material of that control rod that doesn't fission. So when I lower them in, I'm absorbing neutrons and slowing down that fission process. I can pull them out if I want to generate more electricity, more neutrons hitting more U-235 atoms, releasing more heat. Those fuel pellets that I showed you that get loaded into fuel rods, this is where the problem starts arising. We say that after a time, even in that little pellet, that might be like a mole's worth of uranium, 6.02 times 10 to the 23rd atoms of uranium. So a little bit of uranium goes a long way, but eventually I've split all those atoms of uranium, and now we call that a spent, a used fuel rod. And every so often I have to take those out and replace them. I have to store those old spent fuel rods somewhere and put new uranium pellets in. And it's these spent fuel rods, those fission fragments, that high-level radioactive waste. This is what we're concerned about when we look at the drawbacks or the negatives of nuclear power. Certainly, there's no combustion in creating that heat. It's not like where I had to burn coal to get the heat to heat the water to make the steam to turn the turbine. There's no direct combustion in the actual production of electricity. Now, if I look at the entire nuclear fuel cycle, remember I had to mine the uranium, I had to build this nuclear power plant, and this is a big operation with a lot of cement, and that uses a lot, creates a lot of carbon dioxide or greenhouse gas emissions. I had to truck all my equipment there, and my trucks were gasoline that emits CO2. So we just want to make sure we can make that fine point distinction. In the direct production of electricity, no combustion. In the entire fuel cycle, yes, I generate greenhouse gases. Let's focus on this cooling tower for a minute. This is kind of what it actually looks like. And if you were an APES student and didn't understand about nuclear power, some people might think that's pollution or harmful emissions coming out of there. That's just water vapor. They have to dissipate. There's a lot of heat generated there, and I'm superheating that water. I have to dissipate or release some of that heat in the form of water vapor. And so in these big cement cooling towers that we see, that's not part of the reactor core. This is the reactor core over here. The cooling towers are just dissipating that heat as water vapor. However, another drawback or negative associated with nuclear power is that sometimes we just release that hot water directly into the environment, and that's known as thermal pollution. So let's talk a little bit about the storage of that nuclear waste. So we have some issues associated with building our nuclear plant. We have thermal pollution. If I discharge warm water directly into the environment, that water may be warmer than the range of tolerance for aquatic organisms, but my big concern is the storage of this nuclear waste. Those fission fragments have to be stored for thousands of years, and this is some updated information by the Union of Concerned Scientists, who do a pretty nice job of researching and keeping us, the general public, informed about the status of nuclear waste in our country. When nuclear waste was, nuclear energy first started scaling up a lot in the 1960s, we thought, whoa, this is just a perfect form of energy. It's going to be so cheap and so easy to generate electricity. Well, part of the issue is that we just kept stockpiling all of those spent fuel rods. And you may remember seeing images from your book or talking about how the spent fuel rods are stored in these pools underwater on site at the nuclear reactor at the individual facilities. Well, that is not a safe long-term storage facility. And even in the short term, the Union of Concerned Scientists, as do many researchers, believe that we need to find a dry cask storage replacement facility as quickly as possible. So the idea is this long-term repository that all the nuclear waste from around the country get deposited in this underground geologic site, a geologic site that is safe from geologic activity like a tectonic subduction zone or a fault line where earthquakes could be happening. It's got to be an area where there isn't a water table very close to the surface in case there were an issue with leaking or contamination of this. So our government in 1982 created an act that said, all right, we're going to build in a little bit of time, but by 1998, we're going to have a permanent repository and begin transferring all the nuclear waste to that site. That still hasn't happened. And again, that is a concern to all of us because all of that waste is being stored, high-level radioactive waste is being stored on site at what is currently about 97 different facilities. There is some talk as a solution of reprocessing nuclear waste. The risk associated with that is that we could actually create weapons-grade plutonium. Understand that those initial waste products that we looked at, those fission fragments, all this waste from the spent fuel rods that we're storing, those things continue to undergo radioactive decay until they get to a stable isotope. And that's what's taking thousands of years. The concern about reprocessing to try to reuse some of that fuel is that we could turn it into weapons-grade plutonium, and bad actors could access that plutonium and with very minimal effort and no skill or research into the field of nuclear fuel enrichment have the ability to create a nuclear weapon. So the other big thing you probably remember about our concern about nuclear power is that we got a couple of nuclear power plant accidents. The first one of those was 3 Mile Island in Pennsylvania. It was in 1979, the most serious accident ever to happen in the United States. And certainly proponents of nuclear power would say, yeah, the accidents are just pretty rare. And that's absolutely true. Accidents are very rare. There wasn't a lot of discharge of radioactive material during the 3 Mile Island accident, but it really concerned a lot of people. There were a lot of pregnant women in the area that they weren't told right away, should I evacuate, should I not evacuate? Do we have a good plan in place around our nuclear power plants? If there is an accident, do we have an evacuation plan and a system in place to quickly and safely remove people from the area while we clean up? So because of the impending dangers of climate change that are now rapidly unfolding in front of us, many scientists that at the time of the 3 Mile Island accident really suggested we proceed with caution are now revisiting nuclear power because of the zero carbon emissions. There is no combustion. These points are just a bit outdated, but it's a nice map because it shows you the exact location of where most nuclear power plants are. I think we're currently at about 97 functioning. There may be a couple on the map here that have been decommissioned. There has been over over the last number of years a new facility on site to be constructed in Georgia, but they are years and billions of dollars behind schedule and budget, so a little hard to know what's going to happen with that. But other than that, we really haven't built new nuclear facilities since the 3 Mile Island accident, and your generation, to a large extent, will be making a decision based on, I guess, how you vote or how you inform your decision makers about your opinion about nuclear power. Another accident you probably remember hearing about was Fukushima in Japan. This was not a human error. It was a result of a tsunami that was triggered by an earthquake that you understand how the devastating nature of that tsunami wave. The tsunami crashed into the Fukushima nuclear power plant, and there was a partial meltdown and release of a large amount of radioactive material. That radioactive material can be transferred through the air, or it can be transferred through air currents, or it can be transferred through the water, through ocean waves. So even though you may not live near a nuclear power plant, and many of us do, we still are at risk for radioactive fallout if there is an accident in another place. And then the most infamous of nuclear power plant accidents, and what is probably judged to be the worst nuclear disaster in history, is the Chernobyl disaster. Here you see a picture of the reactor. The reactor had a core was compromised as a result of the meltdown at Chernobyl. And we hear about an explosion that happened at Chernobyl. It was not a nuclear, wasn't an explosion like a nuclear bomb. There isn't enough fissionable material for a nuclear power plant to explode like you would think of in a nuclear bomb. What happened was that all that cooling water that cools the reactor core instantly vaporized, and that buildup of vapor pressure blew the top off of the reactor core, and there was a release of radioactive contamination that ultimately precipitated. And you can see how that cloud spread. This is not a very scientific scale. It's just the darker the color is relative to what a normal level of radiation would be. Remember, uranium is a naturally occurring element in the ground. When we studied indoor air pollution, we talked about radon. That radioactive gas is the #1 cause of lung cancer. So I could live in an area nowhere near a nuclear power plant and get some low level dose or exposure to radioactive material by natural means. Maybe it's present in the food that I eat or the water that I drink. That's certainly a big issue even today for areas around Chernobyl, because that radiation can precipitate out of the air and accumulate in soil and water. Let's just do a quick check for understanding. I think I have one multiple choice here and then a little bit of a discussion question. So compared to a coal-fired power plant that produces the same amount of energy, a nuclear power plant generates more of what? And the answer is thermal pollution. All of the rest of these choices are all things that are emitted through combustion, and we'll start looking at those tomorrow. Next, we're going to take a look at this idea of being able to justify a statement, kind of like we did with the tar sands and the sugarcane. So I've given you 2 statements, and it's kind of clearing up some misconceptions that students might have about nuclear power and emissions. So for each remark, provide one justification for your position. Nuclear power plants produce no dangerous solid waste. Do you agree or disagree with that? And then how are you going to justify your position? And since we know that not very many students are watching the lectures live, I'm going to just keep going and not give a lot of wait time because most of you can stop the video and write that. So I would have to disagree with this. There's no way that I could agree that they produce no dangerous solid waste. So I got 1 point for disagreeing with a correct justification, talking about how the radioactive waste must be stored for a long period of time. It was an integral part of making my case there. I could talk about those spent fuel rods being highly radioactive. Even the personal protective equipment that a worker in a nuclear power plant would wear could be considered radioactive waste that has to be disposed of properly. The second statement, using nuclear power plants avoids the release of greenhouse gases. Here, you could make a case and justify it either by agreeing or disagreeing with that statement. I could agree with it because no fossil fuels are burned, but if I look at the entire fuel cycle, I could disagree with it, saying that in the mining, transport, enrichment, all of the processes involved in getting electricity from nuclear power, that there are greenhouse gases emitted. And remember that those cooling towers were releasing water vapor. Technically, water vapor is a greenhouse gas. Let's move on next to energy from biomass. And I want to clarify from the beginning, and I'll make this point a couple times. We've already talked about biomass from wood. We focused on how people in the developing countries use wood or charcoal as a source of energy. Kind of leave that separate for today. Technically, that's biomass, right? It's plant material that I'm getting energy from. We're really going to focus in our discussion today on ethanol, biomass, turning biomass into ethanol and using that ethanol for energy production. So let's go through the process by which we get energy from biomass, starting with the grain crop, and turn that into ethanol. Well, ethanol is an alcohol, and it's made from fermenting sugars. We'll come back to the process in a minute. In the United States, most of our sugar that we get to make that ethanol comes from corn. And as you look at in Brazil, we had that sugarcane question in with the tar sands. Brazil uses a lot of ethanol biomass production. Most of their sugars that they turn into ethanol come from sugarcane. Typically, what we do is we take that alcohol, that ethanol, and we mix it in with gasoline and make gasohol. When you go to the gas pump, you may see there may be different blends, different percentages of ethanol. A lot of that is determined by farm subsidies and energy subsidies. And in the northern climates, winter, because different mixes work better in the cold, you may see an option where there's no ethanol mixed in it at all, and that would be a more expensive fuel. So just a quick reminder of this process of fermentation. Glucose, yeast are utilizing that glucose as a source of energy. Just like I eat a plant and I utilize that glucose in cellular respiration to get energy to run all my cellular activities, ethanol, yeast use that glucose for their process, but in the production of ethanol fermentation or alcohol fermentation, that's an anaerobic condition. So it's kind of like respiration, but without oxygen. That's where that ethanol is coming from, and carbon dioxide as a byproduct. So let's take a look at the benefit of biofuels, because so far these are looking pretty good. We want to look at the entire life cycle. Remember, that's a big idea to look at, and even compare apples to apples of all of my different energy resources. So the benefits are it's renewable. I can always grow more crop, and it's what we call new carbon. I'm going to get into that new carbon in a minute, because remember, tar sands were old carbon. So we'll come back and compare those in just a second. So remember, when I grow my corn plant, it's undergoing photosynthesis, and it takes in carbon dioxide from the atmosphere during the process of photosynthesis. And most of the actual sugars that I want are in the kernel of the plant. But I harvest that corn crop, I transport it into this facility where it's being converted into ethanol. I distribute it with my gasoline. I put it in my car. I burn the gasoline. I emit CO2, but the next day another corn plant's going to take that same CO2 back in. So when we talk about new carbon, we're talking about carbon that was just removed from the atmosphere by that plant that I'm using as a source of sugar, and that same molecule of CO2 gets emitted back to the atmosphere again. Let's look at it in a slightly different way in terms of that photosynthesis equation. So photosynthesis takes out CO2, turns it into a sugar. I harvest that sugar from the corn plant. I turn it into a molecule of ethanol and alcohol. I burn that ethanol in my car tank and return that same molecule of CO2. It's what we refer to as carbon neutral. So in a perfect world, biomass ethanol production from biomass would be carbon neutral. The amount of carbon I emit from burning that ethanol would be equal or balanced out by the carbon that was taken in by that plant through photosynthesis to begin with. So we know that corn is renewable. Here's a beautiful cornfield that I can grow again every year. It's kind of rustling in the wind. Oh, there's Charlie coming out of the cornfield. Hi, Charlie. If we really want to understand what new carbon is, we probably better make sure we contrast it with what old carbon is. So here's the old carbon, my fossil fuels down here. We saw this diagram recently when we reviewed the carbon cycle. Just a quick update. We have a little carbon going into the atmosphere. This is representing live volcanic activity. It doesn't contribute overall to increased concentrations of carbon in the atmosphere. And then we have this cool process of photosynthesis and cell respiration that overscales on our planet throughout the year. Those things balance each other. I don't really have a lot of difference between how much CO2 is taken out during photosynthesis and how much of it is put back in through cellular respiration. So the fossil fuels here are a big concern to us in understanding how we are upsetting the balance of carbon dioxide in the atmosphere. Remember that these carbon atoms are not currently part of the carbon cycle. There's no way that this carbon is ever leaving deep within that sedimentary rock unless I dig it out, mine it, and burn it, combust it in a combustion reaction. So we're adding an enormous amount of extra carbon to the atmosphere, old carbon, that there is no process that complementarily removes that carbon again. There's no way we have enough plants that could accommodate all that extra carbon that we're adding. Let's take a look then at justifying. We're going to look at a couple statements again and see which one is an accurate description of an advantage that biofuels have over fossil fuels. So I'll show you each of these and you can make your choice. An advantage of biofuels over fossil fuels is that burning fossil fuels adds carbon dioxide to the atmosphere and biofuels do not. Or an advantage of biofuels over fossil fuels is that burning fossil fuels adds carbon dioxide, whereas burning biofuels adds no additional carbon dioxide to the atmosphere. And that's the way I want to be able to describe that process or the advantage if I'm writing about it on an FRQ. And it's an area students have struggled with in the past. And I think from reading what students have wrote, here's one of the misconceptions they have. There's this idea, I think that maybe that I just take corn and put it in my gas tank and burn the corn directly. I have to first convert the sugar in the corn to ethanol. And I still have to burn that ethanol. And that I think is what students don't get. They think that, I don't know what they think happens to that ethanol. Whoopsie, but that ethanol is just kind of like a hydrocarbon, right? There's just some extra oxygen in there. So I still have to I mix it in with gasoline. I still put that ethanol in my gas tank. I still burn it and I emit carbon dioxide, but the carbon dioxide can be taken back in by plant right away. Or the carbon dioxide I emitted was the same carbon that plant just took in to make the sugar that was turned into an alcohol. Hopefully you're keeping that straight. So biofuels so far sound pretty good. I really like that idea. That just makes sense to me. About if I take a molecule of CO2 out and put the same thing back in, that's got to be a pretty good situation. Well, there's obviously going to be a downside to everything. And one of them, for our current technique of using corn, a grain crop, for ethanol production, is that most of the sugars are in the kernel. And when we looked at that little cornfield, Charlie was going through that maze and she likes to bring in corn. A lot of the corn plant is stalk and other kind of material it's carbohydrate, but it's more cellulose and lignin and those tough fibrous plant materials that yeast can't easily necessarily break down and turn into ethanol. So it also, when I consider that, it's got a pretty low net energy yield. If I have to prep my cornfield, prep the soil, buy the corn seed, plant the seed, fertilize it, maybe irrigate it, maybe spray pesticides, harvest it, transport it, process it, boy, there's a lot of energy that goes in so that my net energy yield may not be as high as I'd like. One of the biggest concerns a lot of people have is that we know from Unit 5 that we are struggling to meet the food demands of a rapidly growing global population, and should we be using some of the most fertile land in the country to solve our energy needs? So that land could be growing food for people. But the good news is these are really challenges that we can overcome, and it's an exciting, really fascinating area of biochemistry, all the research that's being done in looking at alternative crops, what we would call these cellulose feedstocks, using not just like the kernels with all the sugar in them, but can I grow a non-food-based crop? Can I use waste material or crop residue? Or can I even grow a specific dedicated energy crop that isn't a food crop that's going to be a more sustainable solution for meeting my energy needs? And this can be done, and we're going to take a look at a couple of ways that can be done. I think I'm going to have to advance my video just a little bit here, so bear with me for a second. You are going to go to a research facility associated with the University of Wisconsin-Madison, and I want you to look at the great experimental design just by the layout of the fields they have, because they have all of these different plots that are actually growing my biofuels. So I'm just going to scoot this ahead to our starting point right here.
Isn't the only material that can be used to produce biofuels. Any guesses on what else can be used?
I'm surprised at the number of things we can use to produce biofuels. Out here we're growing things like switchgrass, miscanthus, and cornstover. Here we're standing in switchgrass, which is a monoculture, one species, but we like to think about how crops can grow in mixtures or mix on a landscape to provide ecosystem services like pollination and carbon sequestration that we might not get from just growing the same thing everywhere.
How much carbon does this put back into the soil?
All crops are able to fix carbon dioxide. That's how they make their above ground structures. They take carbon dioxide and turn it into plant material. Perennial grasses, by their nature, put a lot more carbon below ground than our annual crops. We often talk about prairie grasses or many of these perennial grasses as being part of what we consider an inverted forest. That's to say, we see a lot of biomass, but there's a lot more biomass below. We end up over time building our soil carbon resources. So in many instances, we see our annual systems losing carbon over time, and the production that they are putting on is above ground in their grain and not below ground in their root systems.
Time out. That huge field of corn over there looks like you could produce a lot more ethanol than this wispy stuff. What's the deal?
You're right, corn can produce a lot more biomass than the switchgrass varieties we're growing here, but we're interested in the net energy balance. And so when we look at yield, but balance it with the amount of energy it took to produce that yield, we find that the perennial grasses do a better job of maximizing that net energy footprint.
This is kind of like economics. What you're worried about is the net return on the investment.
So we've got some students that are kind of helping out, but look at all of the different plots they had. So they're growing all of these different crops, harvesting them, and doing a great controlled experiment to see how much energy production, what's my net energy yield from all those different crops. Did a really nice job of explaining that for us. So let's take a look at biofuels and see if we can put into practice what we just learned. Describe two economic benefits associated with, I can't see that, two economic problems associated with producing fuel from corn. And there's a big list here, but I want to focus on just a couple of those. A lot of them have to do, for example, with the fact that the price of corn is going to go up, or I might start growing more corn and not grow other kinds of foods. The price of other kinds of food is going to go up, or I'm going to have shortages of a certain kind of food. Maybe I might overuse my agriculture land because we've got such a demand for these energy crops that I'm just going to overuse my land, produce more and more corn. So I guess that was disadvantages associated. You can spend a few more minutes looking at this list. You don't have to know every answer that's on these extensive lists when we show you a response like this. Find a couple of examples that make sense to you and make sure and get those organized in your notes about pros, cons, and sustainable solutions. So next we're going to start looking at energy conservation. This will be the last big topic in the energy unit, and what a great way to wrap up 3 days of talking about energy and what can sometimes be kind of a doomsday prediction with all the carbon dioxide we're creating from burning fossil fuels. There's a lot of really encouraging things happening with green, sustainable design. And you may remember hearing about this organization called LEED. You may have been in a LEED certified building. It stands for Leadership in Energy and Environmental Design. And it's a worldwide ranking system. They help everything from an individual person that wants to build a new residential home to a commercial office building or a biofuel research center. And they help them make those, design them in a sustainable way. The goal of any green design is to provide healthy living spaces for people both to live and work. And the main kind of summary of the main strategies that would be incorporated, certainly reduce energy use, safe and sustainable building materials, water conservation, waste reduction, and whenever possible, locally sourced materials. Let's dig in a little bit to some specific examples that you want to put on your note sheet and be able to identify a strategy and describe how that leads to a more healthy, sustainable living environment. You talked about passive solar heating and cooling with Dr. Sowell. Let's just quick review how that can help me in a more sustainable energy system. I can have big south-facing windows that allow the winter sun to come in and reduce my heating costs, but a roof overhang that shields that sun in the summer and reduces my air conditioning costs. Whenever possible, I want to get really creative with my lighting. I want to have as much natural lighting and reduce the need for external electric lamps and additional lighting to reduce the amount of energy that I use. I can super insulate my home or have very efficient windows that allow less heat or cool air conditioning air to escape. I can use a rooftop garden that really accomplishes a number of my green sustainable design goals. First of all, maybe if this is my office building, I could be growing food. Maybe I have a cafeteria in my office building and that food could be used in the preparation of food in the cafeteria. But in addition to that, this helps me fulfill some of my water conservation goals in green design. That water can infiltrate. I could capture that water, then rather than allowing it to run off, I could capture it and use that as gray water to run the flushing of toilets in my office building. I could use really creative landscaping, not just for providing shade for trees, but I could make sure that my landscaping incorporates all native species. They're already going to be adapted to the water and the soil conditions of that area, so I don't need to use fertilizer or maybe not even pesticides or additional irrigation water. I can use terracing or some type of technique to capture water runoff and again recycle that water to use in my building. And there's a lot of things I can do, but like I said, with insulation and strategically placed windows, but even with incorporating those passive solar ideas into my window shades or window blinds, these are light filtering window shades that again allow light to come in, reduce my lighting costs and the energy associated with that, but they're still keeping out the glare and some of the heat from the sun. In cold climates, we often have a thick fabric fold down shade so that at night, for example, I can fold down that thick fabric insulated shade to hold in the heat, but then just open it up during the day to let the sun. You probably have heard of smart appliances. We have smartphones, we have smart TVs. Many of you have maybe some of these other smart appliances in your home, but the idea is, especially as we look at rebuilding urban areas or any new construction that's happening, trying to get organizations like the LEED organization in there to help people best design long-term sustainable buildings, the economic benefits, it might cost me a little bit more upfront to implement some of these strategies, but over the life cycle of that building, I recover my costs very quickly with massive savings in energy and water and waste reduction. So the idea of a smart home that's all connected to my smart meter and giving me constant feedback about my energy consumption. Right now, most of us have meters that are located on the outside of our house. You guys probably have never looked at your electrical meter. It's like this idea of how much energy we're using and what we're paying for it is hidden and a big secret. We know that if people could see that meter spinning and there were a dollar sign of it on it, we would be incentivized to try to reduce our energy consumption. So a smart refrigerator that will allow me to see inside of it without opening it. Every time I open the refrigerator, all that cold air escapes and that refrigerator has to work really hard to cool things back down. Many of us probably already have this ability to schedule an appliance like a washing machine or a washing machine or a dishwasher, or maybe if I'm charging my electric vehicle in my garage, to program that to run at a time when electrical demand is low and rates are usually lower. What we want to do as we solve our energy needs for a growing population and a more affluent population that will use more energy per capita is we want to avoid having to build huge energy facilities that have to meet these peak demands when everybody's using a ton of energy. If we could take that energy usage and spread it out throughout the day, I can get by without building as big an energy plant with as big a capacity because I don't have those big peaks and drops, and I've leveled out that demand. A lot of us can already do this as well. From my smartphone, I can leave work and say, turn the thermostat up so that by the time I get home, it's at the desired temperature. Or I can check and make sure I turn my air conditioning up and so that it's not cooling a house that nobody's going to be in for 8 or 10 hours. The last thing we'll look at in terms of green design or sustainable design are the actual building materials that I use. Am I buying wood that has been produced sustainably, or maybe I can use alternate sources of wood like bamboo for some of my wood needs in my home? And an area that a lot of us really don't think about, what type of fabrics or carpeting or what is my mattress made of? What are the paints that I'm using or the glues or adhesives and stains or any organic solvents that I'm using in the construction of my home? They often have volatile organic chemicals that will off-gas and become harmful indoor air pollutants. And again, we'll dig into the actual effects of that in the next 2 days on air pollution. So the last thing that we'll talk about in terms of energy conservation is trying to save energy where we use it the most, and that's in transportation. We're going to take a look at 3 different types of vehicles and compare and contrast them to like a traditional car, what we sometimes call an ICE vehicle. That stands for internal combustion engine. So a regular old car that many of us may drive that burns gasoline and gasoline only. The first of those is a conventional hybrid. This has an ICE internal combustion engine, just like a regular normal car, but it also has an electric motor and battery. And I want to make sure we clear up a misconception here, because many students think they see that word electric and they think that this is a car that's being plugged into a socket and that battery is charged with electricity. And that is not the case. This car has an internal combustion engine and it has a battery, an electric motor that's charging that battery. So if I stop at a stop sign for a couple of minutes, my internal combustion engine can shut off and I can keep my air conditioning and radio running by my battery. The other type of hybrid is a plug-in hybrid. This still also has an internal combustion engine, but it has a second, more powerful battery. And that plug-in hybrid, I can plug into a regular outlet or a designated charging station and charge it with electricity. This is beneficial because if I have to drive 100 miles on a trip to get to grandma's house and I can get that entire way without burning any gasoline, and simply by using the energy by charging my battery, I have greatly reduced my emissions. It's a much more efficient process because I use less gasoline to get the same miles driven. And then we have the battery electric or plug-in vehicle. These have no internal combustion engine whatsoever. The battery electric vehicle uses electricity stored in a large battery pack to power an electric motor. The batteries are recharged using grid electricity from a wall outlet or a designated charging unit. And one of the negatives that is often presented about a battery electric vehicle is that if I'm charging it from a wall outlet and that electricity came from burning coal, then I still created carbon dioxide. It's a true statement, but if we're going to compare it to an ICE vehicle, the comparison almost doesn't really hold water or isn't valid, because to get the same miles driven, the emissions from that charging that battery are much smaller than the emissions from burning the gasoline. And we can charge that from a grid system that is generating electricity from renewable sources like wind or solar that didn't have those emissions that coal had to begin with. Another valid concern about a battery electric vehicle is the batteries, and they often create a solid waste problem. There could be heavy metals in there, and it's just an area that we really need a lot more research and development on. We need to build better batteries for better energy storage, and we talked about that with renewable resources as well. This is just really a cool schematic to bring out that point. This is Oak Ridge National Laboratory, which is a government energy research facility in Tennessee, and I think the reason I wanted to share it is there's this overall move towards green, sustainable energy and transportation, and companies are realizing that, like, if I have a LEED certified apartment building, I might attract a client, a renter that really is seeking out, a consumer that is seeking out that type of living space, and I might have an easier time renting those apartments in my LEED certified building. If I'm providing a way for my employees to charge their car at work, this is something that your generation as employees of the future, the people that are going to be hiring you are cognizant of the fact that these are the type of jobs that you are seeking. seeking out and that you want to work in a facility that's going to provide you these opportunities. So a quick comparison of all these different vehicles. Here's my ICE vehicle, my conventional vehicle that uses only gasoline. So there's a lot of gasoline and emissions. I have my hybrid vehicle, uses a little less gasoline because it has a battery. My plug-in hybrid with more batteries, so a very small amount of gasoline. And finally, my all-electric battery vehicle, no emissions because it's got that big battery pack. As we're talking about this idea of sustainable development and transportation, let's bring that together with sustainable design and talk about how if we're like looking at redesigning large urban areas, I can incorporate both of those ideas. Sustainable transportation built in with my sustainable buildings, and then we'll all move and live in that city. I can have this bicycle benefit sticker. You may have this in your community. If I have that sticker on my bike helmet and I go to my local grocery store or coffee shop, I get a discount for having that. They don't want, there's a lot of problems in urban areas with congestion, and I don't want to take that valuable space and have to build parking garages and parking spaces, and I can park a lot of bikes in a pretty small space. When I'm redesigning those urban areas, I can have very large, very clearly designated, controlled bike paths so that people realize that it's easy for them to get safely to their place of employment on their bicycle. Maybe my employer or my community provides a safe storage out of the elements for me to store my bike while I'm at work. Maybe they, in this new urban planning, have integrated walkways and bike pathways and a place where there's emission-free public transportation dropping people off. But this might be an area that is free from internal combustion vehicles to begin with in terms of improving air quality in those urban areas. I could have a commuter park and ride. So before my group of people working in this office building all drive into the city and don't have a place to park our car, we stop and most of us leave our cars in the commuter parking lot, and then the rest of us all get in one car and carpool in a carpool lane where there's less traffic and perhaps I'm not paying tolls. All really good ideas for redesigning urban transportation. Let's do a quick check-in for understanding on that. Identify 2 strategies that a government could implement to encourage the use of battery electric vehicles. Again, I'm not going to take a long time because most of you are probably stopping the video while you're thinking about that. And almost all of these really revolve around financial incentives. So we talked about fossil fuel subsidies. Well, maybe I have a subsidy for battery electric vehicles for them to research and develop better batteries. Maybe I put a tax on gasoline so that people would have more of an incentive to buy a car that didn't use gasoline. Maybe I get a rebate on my taxes when I show a receipt that I purchased a battery electric vehicle. There's a couple that deal with making those charging stations more accessible. So all really good strategies that you want to make sure you have organized in your notes. So a quick debrief and summary of nuclear power, some of the positives and negatives. No emissions, but we have the negatives are that it was non-renewable. There's a potential for a radioactive fallout from a nuclear accident. I've got all that high-level radioactive waste that has to be stored for thousands of years, and thermal pollution. The exciting thing is that there is research and development going on in providing and making smaller, safer, cheaper nuclear reactors to try to overcome our use of fossil fuels. In terms of biomass, focusing on ethanol, it's renewable. Remember that current grain crops may not be sustainable, but I do have those feedstocks that I can grow with much less impact. We have new carbon, so we're not adding to the overall carbon. Just to remember, if we're talking about wood itself, there are other issues, but we really focus today on biomass ethanol production. And again, lots of great opportunities in research and development of feedstocks for ethanol production. So we looked at a lot of different learning targets today: nuclear power, how it's generated, nuclear power accidents, ethanol production. We already talked about biomass, and some conservation strategies. And certainly I hope a lot of sustainable solutions. I'm going to leave you with one last homework question where you're going to look at the project by the Fremont High School of employing a green new roof. And you can skip this first one on carbon footprint because they gave you the definition in the article. So we'll grade this question tomorrow. It is your last homework assignment. Keep looking at how you're going to get yourself organized, and there's going to be a lot more information coming soon about exam prep week. Have a fabulous rest of your day, guys. Good luck in preparing for your energy part of your exam. See you later. Hi, everybody. Welcome to the APES virtual classroom. I'm glad that you could join me again. I'm Ms. Fassler, and I teach APES in Marshfield, Wisconsin. Let's start with the homework that you did last night. You looked at a question that was a really great combination of some energy and sustainable design ideas. The students at Fremont High School want to plan a new green building. And so the first prompt that I asked you to look at was to identify one way the school's heating system is likely to add to the school's carbon footprint. You were told in the article that the school used fossil fuels. And so there were really only 2 ways that it could contribute to the carbon footprint. Remember that we always have to burn or combust that fossil fuel, and it could either release carbon dioxide or incomplete combustion of that fuel could release carbon monoxide. Only 2 possible responses. Next, describe one realistic way to reduce the contribution of the heating system to the school's carbon footprint. And the key thing I want to point out on the rubric here is that you couldn't just say, oh, one thing that the school could do would be to use solar energy, because it didn't necessarily state that they quit using their fossil fuel. So it would have to be switched to a more renewable form of energy, decrease the temperature of the thermostat. You could have gone for purchasing carbon offset points or offset credits. And then there's a whole range of different things you could have mentioned having to do with the efficiency, passive solar or the green roof or double pane windows, south-facing windows. When you are looking at your notes and starting to make your lists and organize your notes, keep in mind that you don't need to have every example that's listed on a rubric. You want to pick ideas that kind of make sense and resonate with you and that are going to get you targeted right to a good solution. Next was to identify 2 environmental benefits of a living green roof. We talked about a few of these, and there's a few on here we didn't specifically mention, but you may have used. We talked about the fact that it provides insulation and could reduce heating or cooling costs. It's an area that I could produce locally grown food. We talked about it filtering stormwater runoff or reducing the amount of runoff. Then you'll see a few other examples as well. You can always, and I suggest that you go through some of these lists in a little bit more detail when we're done, and you can process things a little bit. And again, pick out examples that are really meaningful to you. Describe 2 practices the cafeteria's food service could use to decrease the environmental impact at Fremont High. And notice that term described, I have to make sure that I'm describing, I can't just identify the practice. I can't just say offer more vegetarian options. I have to make sure I describe how that's going to decrease my environmental impact. For example, I could use locally sourced foods, which would decrease the amount of gas that I had to burn in transporting that food great distances. I could compost my food waste, which would decrease the amount of waste going to a landfill. And again, lots of options here. Pick out a couple that kind of make sense to you, maybe things that you're already practicing or that your school is doing. I like the idea of the refillable water bottle stations. Next, discuss 2 benefits of using native plants for landscaping at Fremont High School. We mentioned a few of these yesterday. Remember, most of them kind of focus around the fact that those native plants are better adapted to their environment. Therefore, they need less pesticides, less water, less fertilizer. And again, because I'm discussing that benefit, I'm stating something and then discussing why that is a benefit. That because APES is a real nice transition term there. You can see a few other examples that they gave as well. And finally, in letter E, during the renovation, the carpeting is going to be replaced. Discuss one environmental benefit of using flooring made from plant materials such as cork or bamboo instead of carpet made from synthetic fiber. And again, half of the battle, guys, is making sure you read that question really carefully, because if I didn't read and take the time to process what the question was really asking me, it really decreased the likelihood that I'm going to answer it in an adequate way to earn a point. So I had to make sure that I was doing a comparison. In other words, plant material like bamboo is more compostable or biodegradable than the synthetic fibers of the carpeting. The plant-based materials require less fossil fuel or toxic chemicals in production than the synthetic fibers of the carpet. So lots of different options you could go with there. Our discussion today on air pollution is really going to focus on this point that you may be still a little bit iffy on. So where are we going today? Well, first of all, remember your 2 questions on your exam on Monday, May 18. And Dr. Sowell and I have been kind of starting to prompt you about what that day is going to look like. You've been getting emails from the College Board about how can you start to prepare for that. We're going to have more tools and tricks and tips for you as we proceed through the next few days. So today we are starting in on Unit 7 on atmospheric pollution. Air is a natural resource that covers the earth and crosses many system boundaries. That could even be geopolitical boundaries. And it's what makes air pollution really different than other kinds of pollution. The air is a commons. So if, for example, I'm exposed to a toxin in my drinking water, I might, well, that's a bad situation. And while I'm working on remedying that situation, I have an alternative. I could maybe go buy bottled water, or maybe my community is trucking water in that I can go to a station and fill big jugs. But if there's a toxin in the air that I'm breathing every minute of every day of every year of my life. And there's not really anything I don't have a lot of control over some of the pollutants in air, and not oftentimes a good strategy to avoid that. We'll take a look at the difference between indoor and outdoor air pollution. And today, as we go through these first 4 topics, we're really going to focus on that outdoor air pollution. And then tomorrow with Dr. Sowell, we'll wrap up all of the review by looking at indoor air pollution. Let's begin with sort of a general overview to remind you of some of these different pollutants and where they come from. Remember that a primary pollutant is something emitted directly from its source. And usually that's combustion of some type. It could be these things like carbon, sulfur, or nitrogen oxides. It could be a hydrocarbon. That's what we're talking about when we use that acronym VOCs, volatile organic compounds or chemicals. We're going to look at them in a little bit. A primary pollutant could be a suspended particle. We're going to refer to that as particulate matter. Sometimes the source of those primary pollutants is a natural source. We did a quick review when we were looking at new carbon yesterday, and said volcanoes have this tiny little trickle of natural carbon dioxide. It could be from combusting gasoline in my vehicle, a fossil fuel. So certainly I get carbon dioxide. The main other oxide gas from gasoline is NOx. Here's a coal burning plant that releases carbon dioxide. We tend to label coal as releasing mostly the SOx compounds, gasoline mostly NOx. There's also that particulate matter and some heavy metals present in coal as well. Not that those compounds can't be present in all fossil fuels, but our APES curriculum tends to kind of classify NOx mostly from gasoline, SOx mostly from coal. And then we have these secondary pollutants that form as a result of other gases in the atmosphere reacting. We're going to focus today on only one secondary pollutant, ozone, and then you'll look at some of those acids tomorrow. Let's just do a quick checkup of those oxide gases. All of these are those primary pollutants, and make sure that you're clear on a source and a human impact. And again, kind of modeling for you how you want to organize notes for this unit on air pollution. What's the pollutant? What's the source of it? Where does it come from? Can I describe the process by which that gas gets into the atmosphere, and then some of the impacts of it? We talked about carbon monoxide in the footprint of Fremont High. Remember, that's when my furnace or my gas isn't being burned at quite high enough temperature, or something's not working right, and instead of carbon dioxide, I get carbon monoxide. The thing about carbon monoxide, you're going to see a lot of common human health impacts for all of these pollutants, a little bit generic, some of them more specific. But the thing about carbon monoxide is it interferes with the ability of hemoglobin to transport oxygen. So my brain gets deprived of oxygen, and it could lead to unconsciousness and even death. Carbon dioxide, we have the natural source from volcanoes. We certainly get it when we have decomposition of organic matter or cellular respiration. But remember from our carbon cycle diagram that the combustion of hydrocarbons, of fossil fuels, is a disruption to the carbon cycle and is adding carbon dioxide that has no process that complementary removes it. Sure, photosynthesis removes CO2, but there's not enough plants to keep removing all the additional CO2 that we're adding. There's no direct human health impact of breathing carbon dioxide, but certainly many increased death rates linked to global warming and climate change as a result of adding more carbon dioxide. These SOx molecules, we want to avoid committing to a subscript here. There's a lot of pretty complex chemical reactions going on here, and as an introductory college level environmental science course, our goal is to give kind of a broad overview of these processes, and in a more advanced chemistry class, you'll dig into the detail of those reactions. So these sulfur oxide compounds come from combustion of fossil fuels, mostly coal, and again, you can see the list of potential human health impacts, and the nitrogen oxide compounds, mostly gasoline, and similar human health impacts. We're going to talk about all these more as we move through the lesson. Let's look at one quick question that's 2 simple parts of a prompt from last year's free response test. The visibility in national parks can be affected by many different air pollutants. And my graph here, there's some calculations they did on the graph last year, but it's showing me 4 big national parks and the visibility in miles, and the historic visibility, how far when I'm standing on the top of the ridge, how many miles can I see? And I can see that based on an average throughout from historical data, the visibility has greatly decreased. The national park system recognizes this as a pretty big problem and is looking at some ways to mitigate it, but because visitation is up and we all like to drive our cars through the park, there's a big decrease in visibility. One primary pollutant, that should be pretty easy. You could have listed any of the carbon, nitrogen, or sulfur oxide compounds. There's a few others there. Like I said, we'll look at VOCs and particulate matter in more detail. And then to describe how that primary pollutant becomes part of the atmosphere, gotta have a verb there. And if it's something to do with fossil fuels, I have to burn or combust them. So you can see that that's mostly, I'm guessing where most of you went was something about burning fossil fuels, releasing those. The next topic that we're going to look at is photochemical smog. And you probably remember this is one of the more challenging topics. This is a perfect example of where hopefully in your college level chemistry class, you get an opportunity to dig into the process in a little more detail. So the term photochemical smog, that's kind of like a soup, a mixture of really harmful pollutants. The major component of that is ozone. And we can use those terms synonymously. If I'm writing about this on an FRQ, I can say ozone or O3. I can say ground level ozone. We refer to that as tropospheric ozone to distinguish it from the good stratospheric ozone that blocks incoming UV radiation. And I can just call it smog or photochemical smog. So the first thing we want to do is identify the reactants. What are the ingredients that are necessary to form this ozone? Well, the first thing I need is that NOx that's emitted from the gasoline. I need volatile organic chemicals, VOCs. And if you see the acronym VOC on the exam, of course, they're going to tell you what that means. If you just want to write about VOCs, you can use that acronym. We're going to dig into that in just a minute. And finally, I need sunlight. The photo part of the term photochemical smog is the fact that sunlight is involved. So that's pretty straightforward. 3 different things, NOx, VOCs, and sunlight form ozone, O3. Now what we want to do is focus on describing the process. Just like we identified a primary pollutant and then describe the process by which it got into the atmosphere. Now that I know what those ingredients or reactants are, I have to describe how that gets turned into ozone. So the first thing is the sunlight. This UV light strikes a molecule of NOx and it kicks off an individual atom of oxygen. That individual atom of oxygen combines with a molecule of oxygen gas, 21% of our atmosphere is oxygen, so there's plenty of that going around. And all together then, oxygen, O plus O2 yields O3. So if I'm going to describe the process, oh, wait a minute. You're probably going, hey, Fassler, what's the deal here? You keep talking about those VOCs, but you never describe how those enter into the reaction that makes ozone. So this is where we need to make a clear distinction between simply identifying that VOCs are important in creating photochemical smog, that's that soup of chemicals, and being able to describe this two-step process by which ozone forms. Let's repeat that to make sure you have it down and you can get that in your notes. Sunlight, UV energy, strikes a molecule of that NOx gas emitted from gasoline, that knocks off an individual atom of oxygen that combines with O2 to form O3. So you could probably have that equation in your notes as well. What happens then is this is a secondary pollutant because it formed between these reactions in the atmosphere, and it's a pretty nasty pollutant. I have some of these very similar human health effects that I talked about from exposure to carbon monoxide or NOx or SOx, but I'm adding a couple other things here. I'm starting to look at increased chest pain and pulmonary inflammation, increased risk of heart attacks. So now I'm going from kind of respiratory things to cardiovascular. Hold on to that thought because we're going to dig into that in a little bit more detail when we look at particulate matter. So even though I don't need to know the complex series of reactions that are going on with those volatile organic compounds in photochemical smog, I just need to identify their ingredient. They're still a primary pollutant and pose problems in and of themselves. So let's break apart what this word, this acronym volatile organic means. Volatile means, a lot of kids think that means like it's flammable. Oftentimes volatile liquids are flammable, but volatile means it'll easily evaporate. It will really easily go from a liquid to a gas. Like water evaporates, a puddle evaporates, and it's water vapor. An organic compound, a hydrocarbon, like here's a benzene ring, they have pretty low intermolecular forces of attraction holding them together. They're maybe low molecular weight. They will really readily go from liquid to gaseous phase. Remember, anytime that substance gets into the air that I'm breathing, I'm getting constant exposure to it. And that's why VOCs, while an issue in outdoor air pollution, are really a big issue with indoor air pollution. We've already talked about these kind of indirectly when we talked about green building, sustainable building, and that was that point on the rubric about replacing the carpeting in Fremont High School and the fact that a natural material versus a synthetic material that has these organic solvents in it or organic fibers in my carpeting is going to be a lot more sustainable, a lot healthier for me. So it could come from everything from my building material, the varnish in the wood, flooring, or the glues that are used, or the paints. It could be cleaning products that I use. If I spray something and like, ooh, that kind of has a nasty smell to it, well, I can feel that. That means that it's a volatile organic solvent in that cleaning product, and when you spray that, you inhale it. Some of the health effects associated with VOCs, again, you should have in your notes a statement that makes sense to you about increases respiratory problems. It doesn't necessarily, some of these pollutants don't necessarily cause asthma, but they can bring on an asthma attack, or they can exacerbate or make worse the symptoms of my asthma. One of the things about VOCs is because these are organic compounds, some of them, like benzene, is a known carcinogen. It's a cancer-causing agent. But I want to be a little careful because very few, like NOx and SOx, they don't cause cancer. So if I'm organizing this information in a chart, sometimes students kind of like to stick to a rather safe, broad description of a human health effect, unless you want to break down individual gases or pollutants that have different kinds of impacts and what they are. The solutions seem pretty straightforward. Well, I just don't use certain cleaning products, or I don't live in a house that's been made with those things. But unfortunately, if I'm renting an apartment or living in a dorm room, I don't always have much of a say in the type of building materials that I use. So that's often a little difficult. In terms of mitigating, if it is a problem, I could make sure that I'm venting my home a lot or purchase an air purifying system. I'm pretty sure Dr. Saul will go into some detail on that tomorrow. I just wanted to share with you, we're going to talk about the Clean Air Act in just a second, but I wanted to give you a little historical perspective because we're living in a climate right now where there seems to be a real push towards deregulation, and this idea that environmental regulation and economic growth can't be synonymous and live hand in hand. And we know that's not true. We know that as the Clean Air Act and all of our other major legislation was passed, GDP just kept going up and up and up. So these are images from the city of Los Angeles. The Los Angeles Public Library has a great archive of some photojournalists documenting what the air quality was like. And it's important for your generation to realize how bad things were before we passed the Clean Air Act and the Clean Water Act. I'm old enough as a child to remember a time before the Clean Air Act and the Clean Water Act. And I can remember coming out in the morning and being able to literally brush particulate matter off a vehicle that sat outside overnight because there wasn't any legislation on that. And here are people wearing retro throwback gas masks and young people actually petitioning at a city council meeting to improve air quality. This is an image from the Empire State Building in New York City, and it gives you that idea of visibility. When we talked about how visibility in the national parks has decreased, this is what we mean. There's so much pollution in the atmosphere that it limits my ability to see through that cloud of smog. So the Clean Air Act, as you probably remember, is one of our major U.S. cornerstone pieces of legislation. It was passed in 1970 and overwhelmingly supported by the public, by politicians. Everybody agreed that the scenario that we witnessed in those previous pictures was unacceptable, and we needed to do something about it. And it identified these 6, what we often refer to as common pollutants or criterion pollutants. I told my students, and maybe your teacher did, if you remember the acronym NOS class, it's the 6 pollutants: NOx, ozone, SOx, carbon monoxide, not carbon dioxide, lead, and particulates. And look at the amazing results. There's nobody that could argue that the Clean Air Act was hugely successful. The amendments and the 1990 Clean Air Act amendments went even further in starting to address things like acid rain and protecting the beneficial stratospheric ozone. Unfortunately, since 2016, we started to see an increase. We're going to look at particulate matter in a second. We started to see some of the levels of these criterion pollutants start increasing, and one of them that we're really concerned about is particulate matter. So as we start to deregulate and kind of roll back some of these precautions that are put into place to protect us, we will start seeing a low rate of life expectancy. The Centers for Disease Control can quantify the loss of life expectancy because of respiratory and cardiovascular disease associated with breathing polluted air. Let's do a quick check question or two that looks at the topics that we just addressed. One that deals with this kind of complex issue of ozone formation. Nitrogen oxide is produced early in the day. Ozone concentrations peak in the afternoon and are higher in the summer because ozone is produced by chemical reactions between oxygen and sunlight. And I wanted to point out, if we looked back at that first slide with all the cloud of primary pollutants, we would see both NO and NO2. And technically that NO gets converted like as the morning goes on. So I got like, people leaving and driving into work and the office and school, and they're emitting a lot of that NOx. One of the reasons us APES teachers tell you just to use NOx is we don't want you to commit to a subscript there. They're not going to, again, these chemical reactions can get pretty complex, and we're not going to necessarily have to tease out that first it's NO and then that gets converted to NO2. So what are those other things on there? Aldehydes, hydrocarbons, those are the VOCs. So we have NOx, we have some sunlight, and we have VOCs. So notice that a short time after those cars all started driving during that morning rush hour, and pretty soon the hydrocarbons peak, and shortly after I get a peak in VOCs and NOx, the level of ozone starts going up. I use the VOCs and the NOx to create the ozone, and those concentrations go down while the concentration of ozone goes up. So I kind of given it away, but there's a lot to break down in that diagram. Which of the following best explains the pattern in NO concentration? I'll see if you can take a look at that. And you should have got that. That was produced by rush hour traffic. Again, you don't necessarily need to be able to describe in an FRQ that original NO was oxidized into NOx. All you need to conceptualize is what we looked at earlier. NOx is emitted from burning gasoline, and it forms ozone, and that ozone is going to peak a little bit later in the day. The last primary pollutant that we'll take a look at, I think it's the last one, is particulate matter, or PM. This is solid particles of dust or ash, what we call fly. Could even be liquid droplets. It comes from burning fossil fuels. It comes from burning biomass. If you've ever had a campfire, you're burning wood, and a breeze comes along, you might see a lot of that ash and fly coming at you. Forest fires are a big contributor to particulate matter, and even cigarette smoke, because there's a lot of nasty stuff in there that's releasing particulate matter. Oh my gosh, look at those human health effects. That looks pretty straightforward. The thing about particulate matter is that other substances can kind of stick on to those little particles of dust or ash or fly, and then they can be carried by wind currents and deposited. That verb is deposition. They can be deposited, fall out, just like rain, right? They can be deposited a great distance from where that particulate matter was actually generated. When we look at this image, these are not the actual sizes, it's a size comparison. So you can probably picture the size of a fine piece of beach sand, and then relative to that, a human hair, a dust particle, and this is a little tiny soot particle. And on the next slide, we'll look at this in detail. The smaller the diameter, the smaller the size, that is measured in picometers, the smaller the size of the particle, the more harmful it is. And the first thing we might be like, well, I think if it's bigger, it's going to be more harmful. So we'll explain that idea in just a minute. We know that cuts to the Clean Air Act have added to people, that the Clean Air Act has added to people's lives. And again, because we are now increasing that particulate matter again, we hope we don't see a reverse in those great trends that we've established through the passage of the Clean Air Act to begin with. Let's take a look at what happens when I breathe in the solid particulate matter. It's a really dangerous pollutant. Even though my respiratory system has some natural defense mechanisms to block these things, think of like the hairs in your nasal passages, the smaller the particulate matter, the deeper it can work its way into my respiratory system. So that this tiny little particulate matter is actually getting into my lungs. So it's not like if I'm breathing in air where there's a lot of photochemical smog, I can feel that when I breathe it in. It hurts my lungs, but then I'm exhaling that. And it's not that like that gas can't hurt my lungs and cause some damage, but it's not becoming permanently part of my respiratory system. This particulate matter can be embedded in my lungs. And this is where we start getting into cardiovascular disease and pulmonary issues, because this is in these little alveoli of my lungs is where that gas is exchanged, carbon dioxide for oxygen, and that particulate matter can embed itself in those tiny little vessels and constrict them. It can cause inflammation, it can constrict them, and my heart has to work really hard to pump blood through that constricted blood vessel. So particulate matter is one of the most dangerous of the air pollutants, and really one that we think probably contributes to a lowering of life expectancy to the greatest degree. So once we get all of these pollutants, mostly in an urban area, but rural areas are excluded from that. Remember, particulate matter could be soil or dust off of an exposed crop field that I might be getting exposure of air to. I mentioned that we do frac sand mining in Wisconsin. There's a lot of concern for people that live in the area where that sand is mined, that there's a lot of particulate matter in the air, and they simply want somebody to do testing. It's really the value of long-term research, because if we don't know what normal is, we don't know when something exceeds normal. So that idea of long-term monitoring of, in this case, air quality is really important for environmental and human health. So in a temperature inversion, the first thing before we review this is a natural process. What I'm describing to you, whether it's without the inversion or with the inversion, this is a natural climatic event or process that happens in certain areas under certain conditions. The deal is when a thermal inversion naturally forms, any pollution that's in that air gets trapped at ground level. It's not dispersed, and that just means I'm getting a really high concentration of that toxin. So without a temperature inversion, the sun strikes the earth and it warms that air mass near the surface of the earth. We reviewed all this when we looked at weather, and then that warm air mass that's less dense rises. Each of these is a little particle of pollutant, and it disperses all that pollution. It's not like it poof disappears and the pollution was never there, but if I'm down at that ground level breathing that, the dose or concentration that I get is much smaller than if I'm breathing that air during a thermal inversion or a temperature inversion. So what happens here is I have a high pressure system, a normal weather event, and that high pressure pushes down. It's the pressure of all those gas molecules pushing down in the air, and it traps this layer of dense cold air at the bottom. And what happens is it prevents that air mass from rising and dispersing those pollutants. So the inversion, a natural climate event, but if it happens in an urban area where there is a lot of smog, it means that people that live in that area are getting a very high dose or concentration during their normal breathing of those toxins. Let's look at the same scenario, not in a city, but in an area where there's mountains, for example. Again, I have a high pressure system, all that air mass pushing down, and I have forest fires or industry or a lot of vehicle traffic, and people that live in that area are literally choking on that smog. They're getting a high dose or concentration of it. So thermal inversions or temperature inversions are the biggest issue in large urban areas that have a lot of vehicles and that have a lot of sun, because I need sun for photochemical smog, and areas that are warm and dry. That's something you might want to write in your notes. All chemical reactions happen faster in a warm, the warmer it is, the faster that reaction happens. And if I have an area that gets a lot of precipitation, again, the pollutants don't cease to exist. They don't just disappear, but I can sort of wash the atmosphere. And so if I have a lot of those chemicals in the atmosphere, I can sort of wash them out. They may end up falling as acid rain. That's not a good thing, but I'm not breathing them in. That's why a lot of large urban areas, to mitigate some of these problems, may actually do cloud seeding and try to get it to rain to sort of cleanse the atmosphere. This would be representative of what happens in the city of Los Angeles, infamous for its photochemical smog because of a lot of vehicles. And these are the San Gabriel Mountains, so they're blocking the path of that wind. And I get this cool sea breeze coming in off the Pacific Ocean, and it creates this inversion. To invert means to flip. Normally I have warm, then cool air, and the warm air can rise. I flip those layers and have the cold layer of air on the bottom. I think I have a question or two that checks our understanding of that. So I'm going to give you a second to read this question and look at the diagram. And you should have picked that the less dense warm air creates the inversion. Since we're not doing any multiple choice questions on our exam, I'm not going to take the time to talk about multiple choice strategies. Just think of how they could ask this question of me on an exam. I could identify the pollutants that are required. I could be asked to describe the process by which a thermal inversion forms. And so in your notes, it's a couple of simple steps in order to describe that process. Oh my gosh, there's a lot going on there. We'll come back to that color highlighting in a minute. Let's just read the question and answer it to begin with. An air pollution sets up some air pollution monitoring to measure the particulate matter, PM, leaving a farmer's field after crops were harvested and the soil was bare. She set up high volume air samplers 10 meters from the edge of each square field and collected samples weekly for 2 months. When she looked at her data, she was surprised by how much the PM levels varied, both from site to site on a given day and over time at each site. Which of the following parameters would have been the best to measure to help her explain the variation in her results? And again, let's reread the variations. She was surprised how much the data varied from one site to another and from one day to another. And hopefully selected wind direction and speed. That's going to influence how much of that particulate matter blew off and was collected by her air collection sampling device. The next thing I want to do is take a look at the parts of the description that I've highlighted and use this as a good opportunity to talk about experimental design. Remember, one of our learning targets early on was to describe an aspect of a research design and or method used. When you look at that, I think a lot of students aren't really sure what do you mean by research method, design, or measure used. Well, the research question is kind of what she's asking there, highlighted in yellow. I could actually ask that as a hypothesis. Maybe I presented this scenario and they said, based on this, what would have been the researcher's hypothesis? And I'm really focusing in on she wants to look at the particulate matter level after crops were harvested and the soil was bare. So my hypothesis might be that the field with no cover would have a greater amount of particulate matter than a field that had a cover crop left on it. There'd be less wind erosion and that soil blowing around. The measure that she used, she took air samples, high volumes of air samples. The research method that she used, she collected samples weekly for 2 months. So she had some specific parameters. And those are the kind of things you might be asked to give in an FRQ. It might say, describe your research method. And you want to make sure that you're collecting enough samples over a long enough period of time. They might ask me what the independent variable is. We've seen that a lot. That would be the measure of the amount of particulate matter and what her control would have been. Oh, that would have been the field that still had the crop on it, because I want to measure, maybe my question is, what's the value of maintaining a cover crop? And one aspect of that value might be reducing particulate matter and the human health effects associated with that. I put this question in. I think we sort of addressed it before. Dr. Salome addressed this tomorrow as well. But we've talked about burning wood or burning biomass and relate that to particulate matter. And the question here is, one negative impact of the practice is that impact on human health. Which of the following describes a strategy for mitigating that problem? And that would be installing an effective ventilation system. I think I mentioned when we looked at burning wood or biomass that might be even installing a chimney in many developing parts of the world where they use wood or biomass. So we have covered all of the first part of air pollution today. Just a quick review. We looked at coal combustion and the specific pollutants that are released from that. Fossil fuel combustion in general. You're going to go, I didn't even talk about acid rain because I know Dr. Sowell is covering that tomorrow, but we spent a lot of time talking about the process that creates photochemical smog and identifying the ingredients necessary for that. We talked about the human health impacts of it. We looked at the Clean Air Act, and then we looked at carbon dioxide, particulate matter, and what happens during thermal inversions. These were the skills that we really focused on. We looked at the relationship among variables in the data. When we looked at that NO to NO2 to ozone graph, how those concentrations change throughout the day. We looked at the thermal inversion. That would be a good example of being able to explain an environmental concept represented visually. And we looked at describing aspects of a research method, design, and or measure used. Just a reminder to keep looking at all of those emails the College Board is sending you. We're going to start going back over some of those big ideas and more to come during exam prep next week. Thanks so much for joining me as we covered the first half of air pollution. You're done with me for review. Dr. Sowell will be finishing up with indoor air pollution tomorrow. Have a great day, guys. Good luck.
Hello, AP Environmental Science students, and welcome to our last of the review sessions. We're going to finish up Unit 7 today. Next week, we will still be meeting again, and we're going to have some practice exams next week, but more information on that later. So let's take a look again, just a reminder, our exam is May 18th, and you can see the exam times there, and our 2 FRQ questions that we've been practicing. So here's where we're going to go today to finish up Unit 7. So Ms. Bachelor did a wonderful job yesterday talking to you about some outdoor air pollutants, and today we're going to focus on some strategies to maybe mitigate or prevent some of that, and we're also going to look at indoor air pollution. So we're going to look first at indoor air pollutants themselves, reduction of air pollutants, acid rain, and noise pollution. I'm not going to go in that exact order, that's how it's listed in the curriculum. And then we're also going to practice practice number 4, scientific experiments. I'm going to show you several clips of scientists doing scientific work experiments. I'm also going to give you a few chances to kind of describe some potential scientific methods as we go along here. All right, so what do we need to know about our first topic? 7.7 is acid rain. So by the end of this section, you should be able to describe what acid rain is and the effects of the acid rain on the environment. You'll notice that it says acid deposition here. That's just a broader term that can encompass other things other than rain. So snow, sleet, dry, fallout. So acid deposition is just a broader term. Acid rain is more specific. All right, so to get there, we'll talk about the causes and then the effects both on humans and the environment. So Ms. Fassler talked to you about SOx and NOx emissions last time through the burning of fossil fuels and other human activities. We're going to start by looking at those emissions and how they create acid rain. So that can occur naturally. If you think about how SOx might be emitted from something like a volcano, we could have natural acid rain. But what we're going to focus on is the anthropogenic sources of that. And for us, this is a secondary air pollutant. While SOx and NOx might be considered primary, the acid deposition that comes as a result of that is a secondary air pollutant because it's something that's forming through a chemical reaction after the primary is emitted. So what's causing acid rain? This is our SOx and our NOx. So once the SOx and NOx enter the atmosphere, they're going to mix with water to create nitric and sulfuric acid. So in terms of the main sources, so Ms. Fassler mentioned yesterday that a lot of NOx comes from motor vehicle emissions and coal burning power plant emissions. And then SOx mainly is just the coal-fired power plants. Why do we not see as much SOx from motor vehicles? Well, because there's been some concerted effort with legislation and some practices to reduce the amount of sulfur and gasoline. So once these SOx and NOx are emitted, we make the acid rain or the acid deposition, and it can fall down in rural areas and city areas and water and on land and kind of get transported around for a big wider effect than you would think. So let's look at some effects. Well, first of all, the people who are going to be most affected by it are communities that are downwind from coal burning power plants. So this is my coal-fired power plant. Wind is going to blow this way downwind, and this community is going to be most affected. It can corrode man-made structures and buildings. In particular, things like this. The statue is made of limestone, and the acid rain can deteriorate those structures. What does it do to the environment? Well, acidic rain can cause damage to tree leaves and needles, so to reduce the ability of the tree to go through photosynthesis and can cause the tree to die. It can percolate and infiltrate down into the groundwater and affect the groundwater sources, or it can just run off into surface waters. So it can have a wide array of effects once it hits the ground. And once it goes into the soils, 2 things can happen. Number 1, it can increase aluminum toxicity. Acidic soils make aluminum more soluble and more easily taken up by roots, and that can cause some damage to plants. And it can also affect the availability of some nutrients in the soil. That's why farmers always want want to test the pH of their soils before they plant their crops. So let's look at the effect on organisms in particular. So this is the critical pH level for aquatic organisms. This is just a chart showing several aquatic organisms. So let's just take the crayfish, for example. This is saying that below 5.5, the crayfish will not do so well. So this is kind of the critical pH levels that we don't want to go below. So if we think about these things, this is really going back to that concept of range of tolerance. Ms. Fassler talked about that several times in her review sessions, that we have the abiotic factors, whether it's pH or temperature, salinity. There's some kind of abiotic factor in the environment, and there's an optimal range for the species. So here in the middle, this is the optimum temperature range for these fish. They like this temperature. They function perfectly in this temperature. But too high or too low, you get into the zone of stress where they're not functioning properly. And then you get into the zones of intolerance on the final ends where they just cannot live there. So if we think about pH, the same kind of influences. Because pH is so easily measured, and we've all done experiments in which we measure pH, think of an experimental design that you could do. Perhaps what kind of experiment could you do to study the effects of lower pH on things like plants? What kind of data would you collect? What would be your variables? What might be your control group? So, excuse me, this process of looking at an environmental problem like acid rain, if you can think of a way to quantify or measure how that affects the environment, you should always be practicing these experimental design processes. What kind of tools would you need? What kind of setup would you need? How would you control for other effects that you didn't intend? Or how would you replicate your data? So we're going to do this several times today to talk about a scenario and then say, could we pull back and think, well, how could we quantify an experiment of this phenomenon? So here's a little clip from National Geographic that summarizes acid rain.
What is acid rain? Acid rain is any form of precipitation with high levels of nitric and sulfuric acids. It can occur in the form of snow, fog, and even dry materials that settle to earth. Most acid rain is caused by human activities. When people burn fossil fuels, sulfur dioxide and nitrogen oxides are released into the atmosphere. These gases react with water, oxygen, and other substances to form sulfuric and nitric acid. Winds may spread these acidic solutions over hundreds of miles. After it falls to Earth, acid rain enters water systems as runoff and sinks into the ground. This can make water toxic to crayfish, clams, fish, and other aquatic animals. The rest of the food chain, including non-aquatic species such as birds, is often affected as well. Acid rain also harms forests by damaging trees' leaves, robbing the soil of essential nutrients, and making it hard for trees to take up water. By designing cleaner power plants and using fewer fossil fuels, we can reduce the number of pollutants that create acid rain.
So that's just a nice little overview of the idea of acid rain. So let's say we did want to reduce the amount of acid rain. One of the things we might want to think about is how do we reduce the amount of SOx that's entering the atmosphere. So that's what 7.6 is about. 7.6 is about explaining how air pollutants can be reduced at the source as they're being emitted, not in terms of cleaning them up later, but how could we reduce the amount of pollutants coming from the source. We're going to look at two systems coming from cars, so vapor recovery systems and catalytic converters. But we're going to start by looking at two devices that are often used in coal-fired power plants, which are scrubbers and electrostatic precipitators. So let's start with scrubbers. When you think of a scrubber, you should think of a little spray mist bottle like the one in the picture here. So a scrubber system removes or scrubs the SOx and some particulate matter emissions from the gas from a coal-fired power plant and other factories as well. And how does it do it? It sprays this wet slurry of limestone, which is high in calcium carbonate, into that gas, and it causes the sulfur to kind of be collected and drop out to the bottom. So there's less sulfur coming out of the top. It doesn't get rid of all of it, but it reduces a lot of it. And then the sulfur can be collected in a different form and stored somewhere in a landfill, taken somewhere else. So that's how a scrubber works. Here is an example of a factory in India before and after they installed a scrubber. Now you wouldn't be able to see really the decrease in SOx, but what you can see is a really strong decrease in the amount of particulate matter. You can see it was a dramatic effect after they installed it. And if we look at our sulfur dioxide emissions in the United States between 1980 and 2018, we see a 91% decrease. So all of the regulations and policies that the United States has been putting into play have had a dramatic effect on the amount of sulfur in the air. So another device that is often used at coal-fired power plants is an electrostatic precipitator. So in essence, what happens is the smoke comes in through the bottom, the particles are charged, so there's an electrical charge given to them that attaches them to the plate, and then they fall down. So again, you're collecting them into the bottom that can be hauled off. So it works by creating an electrostatic charge, which attaches to the particulates, and as those particulates become charged, they attract to the metal plates and then fall down as dust. Whenever I talk about this, my students always give the analogy of taking a balloon and rubbing it against some fuzzy hair and then holding it over some pieces of paper. The little pieces of paper will get sucked onto the balloon. Very similar device. Electrostatic precipitator. Really going to reduce the amount of particulate matter, PM, from the air. And if we look at PM 2.5, remember this is the number that comes after the PM is about its size. So the smaller the PM number, the more likely it is to get into your bloodstream through your lungs. And we can see there's been about a 40% decrease in this tiny amount or this tiny size particulate matter since 2000. All right, so now let's switch over to cars. On a car, there's a device called a catalytic converter. And the catalytic converter reduces the emissions of 3 harmful compounds in the exhaust. So carbon monoxide, NOx, and then some hydrocarbons. So what does it do is as the exhaust from the engine comes through the catalytic converter, some chemistry goes on here, which you do not need to know for the purposes of the exam, results in water, carbon dioxide, and nitrogen gas. It doesn't completely remove the NOx or the carbon monoxide or the hydrocarbons, but greatly reduces it. So catalytic converters have had a profound effect on the amount of these things in the atmosphere. And while that is not the only thing we've done to reduce carbon monoxide levels, we can see that the amount of carbon monoxide from 1980 to 2018 has had an 83% decrease in the United States. All right, so the second device that's used with vehicles is vapor recovery. So we've all pumped gas at some point, maybe, and if you're pumping gas, you will probably have noticed the smell that's coming out of that. That is the volatile organic compounds, the VOCs that Ms. Fassler talked about last time. So there's a certain nozzle that will actually prevent those fumes from getting into the atmosphere. They actually suck them back up and can store them underground. So why do we care about this? Is because VOCs are really dangerous in terms of their ability to form photochemical smog in some of our urban areas. So to reduce photochemical smog, one way to do that is to reduce the amount of VOCs coming from gas tanks. You can also reduce it by when the truck delivers the gasoline to the gas station. That's another chance for the vapor to get escaped, and they can also do that as well when the gas is delivered. So anytime gas is going in or out of the underground tank, that's when you want to be mindful of minimizing the amount of VOCs that get into the air. All right, so that kind of takes us through outdoor air pollution. Ms. Fassler started the conversation the other day, and I kind of wrapped it up with a few strategies to reduce this pollution. But now we're going to go inside. And sometimes indoor air pollution can be more dangerous than outdoor air pollution in certain cases. And there's some things that we just don't think about on a regular basis. We think about factory smoke and pollution because we can see that it's visible to us. But a lot of times the indoor air quality problems in our homes are invisible. So by the end of this section, we're going to, again, the pattern is the same. We're going to identify pollutants and then describe their effects. So we will look at both natural and anthropogenic sources of indoor air pollution, and then look at health effects on of these pollutions on our bodies. So before we do that, I want to show you a little clip. And as you watch this, I want you to think about how you could design an experiment based on what you learn here. So this is going to present a scenario about indoor air pollution, and think about how could you go about designing an experiment to test something from this video.
Air pollution carries significant risk to human health, and children are particularly vulnerable. The invisible pollutants inside our buildings can lead to much higher pollution levels. However, work by Ishan Tripathi, a high school student and in the class of MIT 2023, and Joseph Aquatra of Cornell University seeks to draw attention to the risk of indoor air pollution to children's health. Indoor air pollution affects adults and children differently. Children spend most of their time indoors in the child breathing zone, an area defined as being up to 1 meter from the floor. This means that seemingly harmless activities in the home, such as laying carpets or painting rooms, can have a different impact on children and thus cause serious health issues. Current ventilation systems work on the assumption of equal distribution of pollutants. Through their research, Tripathi and Aquatra have shown that different pollutants can occur in different layers in the air. They also found that when pollutants such as dust are disturbed, they can be resuspended in the air. The health problems caused by indoor air pollution are severe, but also avoidable. One of the best methods of prevention is proper ventilation. When combined with greater awareness and understanding of the risks, these simple measures are sufficient enough to help reduce risk to children of exposure to indoor air pollutants.
So thinking about that, what kind of experiment could you design? Well, one of the things that I do with my students is one that's pretty common, where we can take a petri dish and put a thin layer of Vaseline on that petri dish and set it out in different places to see how much particulate matter sticks onto the petri dish. So one of the questions that we always look at is how does the height affect the amount of particulate matter pollution in a home? So you can take these petri dishes and put them in different heights in your home. And if every student does that in several heights, we have a good amount of data to analyze, even though the houses are different. So, thinking about what's your independent variable, or our independent variable here would be the height that we place it at. What's your dependent variable would be the amount of PM, the amount of particulate matter that you collect. Well, your methods, just talked about that a little bit of putting the different petri dishes at different heights in your home for maybe 24 hours and then stopping to count them. What factors will you keep constant? Well, you may want to keep constant the amount of petroleum gel you use, or the size of the petri dish, or how long it's been exposed to the air before you close it up. You want to keep a lot of those things constant. What will be your control? Well, I think it would be really useful to take one of the petri dishes and keep it sealed and don't open it up, because there naturally might be some particulate matter found in the petroleum jelly or from when you were applying it in the first place. So having one that's not exposed to indoor air. And then what tools would you use to quantify your observations? We probably would want a microscope or a hand lens or a light, something that you easily see and count the particulate matter. How would you analyze your data? What kind of graph would you generate? What kind of data analysis or statistics would you use? So these are the questions that you want to think about again anytime you're presented with a question that you want to answer scientifically. So let's move to carbon monoxide now. Carbon monoxide is an asphyxiant, and Ms. Fassler talked about this the other day about how it binds with hemoglobin and prevents our body from distributing oxygen to our brain and other places in the body. So this carbon monoxide really comes from burning fossil fuels or biomass. It's colorless, it's odorless, so it's very dangerous, it can't be detected. And again, it's highly toxic because it binds with hemoglobin. This is a particularly harmful event in some developing countries where indoor cooking or heating has to happen, and there might be less ventilation. So we're going to take a look at a little clip in a minute about this particular problem and some ways to solve it. But this smoke that's happening here, not only is there carbon monoxide, but you've got this particulate matter that could get into your lungs and into your bloodstream. This is a little screenshot from Ms. Fassler's talk yesterday. So how could we prevent this? Would there be a way to prevent this from the source, or a way to mitigate the effects? Well, one thing to do would be switch to a cleaner fuel source or to improve the ventilation at homes. But remember that all of these solutions probably have a cost associated with it, and you may want to think about how do socioeconomic factors affect that ability to make that change. One thing to think about, and I always think about when I think about carbon dioxide, is the use of generators. Here in Florida along the East Coast, when we have hurricanes and the power goes out, some people will use generators to provide electricity, and a lot of those generators run on gasoline. Well, unfortunately, sometimes people will bring those generators inside and they can experience carbon monoxide poisoning. So there's a big difference between a developed country using a generator inside for a hurricane versus someone who is cooking and heating their home on a daily basis. So let's take a look at that particular issue. This is from the UN. So now let's switch over to a natural source of indoor air pollutant, which is mold. So mold spores are everywhere. And so a lot of places they land, they just can't grow. But where do they like to grow? In moist, warm conditions, commonly in poorly ventilated areas where it's really humid. A lot of times this happens in a bathroom or in some internal walls where there's a high humidity and not a lot of ventilation. These spores can cause allergic reactions, asthma, and other respiratory issues. And there's really no way to eliminate all the mold or mold spores. They're kind of ubiquitous all over the place. How you control mold is by improving the ventilation in an area or just reducing the moisture content in an area. Next, we're going to go to another anthropogenic source, which is asbestos. So asbestos is a type of particulate matter pollution. It's a naturally occurring material that has these tiny little microscopic fibers, very, very tiny, and they have a unique set of properties. They're very fire resistant and strong. So we use them a lot for construction materials like insulation or as a fire retardant. Unfortunately, once those fibers become inhaled into the lungs, it can cause several cancers and diseases, including mesothelioma. Here are two pictures of some asbestos. So you can see insulation in a house, old insulation, old hot water pipes used to be insulated with asbestos. It's not something that's used anymore. So you're typically only going to find it in older homes or older buildings. This was a part of an FRQ a couple of years ago. The question asked the students to identify the source of the indoor air pollutant and one method for reducing exposure. And so for asbestos, again, the building materials, insulation, and then ways to reduce exposure, safely removing it, sealing it up so it can't affect you, or just leaving it undisturbed, because it's when it's removed and disturbed that those particles get into the air and cause problems. All right, the next anthropogenic source of indoor air pollution are VOCs. And Ms. Fassler talked a lot about these yesterday in terms of being part of photochemical smoke. There's volatile organic compounds. What we're going to talk about today is how VOCs are also emitted indoors from things like furniture, paneling, carpets, adhesive, glues, paints. When you open up a can of paint, you can easily smell that smell. That's a VOC. So there's a lot of things that happen in our homes that we don't think about that can increase the amount of VOCs inside. Why do we care? Well, eye, nose, and throat irritation, headaches, damage to liver, kidney, and central nervous system. So it definitely has some very negative health effects. So one type of VOC is formaldehyde. And one place you can find formaldehyde is in pressed particle board. So instead of using a full piece of wood, you can create particle board by gluing together little chips of wood, almost like pulpwood. And so it's kind of Frankenstein together by little pieces of wood. Well, the glue and adhesives and chemicals used to bind all this particle board can emit VOCs. So a couple of years ago, I was at a state fair here in Florida, and one of the things they had there was a big mobile home that you could go in and tour, to show off, new mobile home. And so we went through there to look around, and I happened to see the sign that was stuck onto the bathroom counter, the kitchen counter, inside the mobile home. So I'm going to read you part of this, and we'll talk about it some more. Some of the building materials used in this home emit formaldehyde. Eyes, nose, and throat irritation, headache, nausea, and a variety of asthma-like symptoms, including shortness of breath, have been reported as a result of formaldehyde exposure. Elderly persons and young children, as well as anyone with a history of asthma, allergies, or lung problems, may be at greater risk. Research is continuing on the possible long-term effects of exposure to formaldehyde. So we kind of go, okay, well, thanks for giving me that little piece of information, but what does it have to do with the mobile home? Next paragraph answers that. Reduced ventilation resulting from energy efficiency standards may allow formaldehyde and other contaminants to accumulate in the indoor air. Additional ventilation to dilute the indoor air may be obtained from a passive or mechanical ventilation system offered by the manufacturer. So it's really interesting here that it's almost like a health warning for a new home. Because we build homes with a lot of these processed particle board woods and carpets and adhesives that use these chemicals, combine that with the fact that we make homes very, very well insulated now. We have lots of insulation, home is very energy efficient. Well, that kind of is good for our heating and cooling costs, but it's bad because any air pollution like formaldehyde that comes into the home stays in the home. So anyway, I thought that was a really interesting case of a VOC coming black. All right, so another air pollution is lead from paints. So even though paint is a liquid, we don't think of that being an air pollutant. What can happen is old paints used to have lead in them. We don't do that anymore. So this is only going to be a problem again in old buildings and old houses. But as that paint starts to peel off, it can create little particulate matter and become inhaled. And anytime you are remodeling or demolishing older homes with older paint, that's when it becomes a problem. The next we're going to look is radon. Radon is a natural indoor air pollutant. This is a naturally forming radioactive gas that comes from the decay of uranium in the rocks in the ground. So the uranium in the soil and in the rocks naturally decays over time. And one of its products is radon. And that radon can get into the house and again kind of be trapped in and cause some very dangerous effects. Not everywhere in the United States experiences the same threat to radon. Here where I am in North Florida, the risk is a little bit lower than if I were up in some of the northern states. So it definitely has to do with the geology of the soil and the ground underneath. So radon typically is going to move up through cracks in the foundation or the basement because that's what's coming in contact with the ground. And once it gets in there, it can build up just like any other indoor air pollution. It can also infiltrate cracks into groundwater pipes, so it could enter the water as well. Unfortunately, radon is the second leading cause of lung cancer in America. So this is a very big threat. That's why we typically see radon detecting kits or radon detectors in homes to monitor that. So taking all that into consideration, the American Lung Association gave a list of guidelines to improve the indoor air quality, and I thought they were worth just looking at. I mean, I know I don't operate a coal-fired power plant, so I don't really have the opportunity to buy a scrubber and stick it on the smokestack, but I do live in this house, and I do have the ability to change things in my own home to improve the air quality in my own home. So here are some of the recommendations. Make it a smoke-free zone. Tobacco smoke is very, very dangerous. That secondhand smoke is very dangerous. It's particulate matter and all of those other chemicals involved. Test it for radon. You know, radon is colorless, tasteless, odorless. It's linked to lung cancer. Like we said, so testing for radon would be really useful. Fixing leaks to discourage mold growth. Remember we said mold grows in really damp, unventilated areas. So, and then take a look at the cleaning supplies you use. Think about what kind of cleaning supplies are producing VOCs, for example, or the pesticides that you might use in your home. Dehumidifiers or an air conditioner to keep the humidity levels low. Because remember, anytime that humidity level goes pretty high, that's when you're going to have more mold growth. Then it talks about buying an air purifier that could capture some of those air pollutants, those air particles, and then to avoid burning wood inside. So this is that indoor air pollution that we saw coming from cooking and heating using biomass inside. So some really good recommendations from the American Lung Association. All right, we're going to end today with noise pollution. Noise pollution is one of those things we really don't think about until we hear it, and sometimes it can have some very dramatic effects. So to get there, we're going to talk about the anthropogenic sources of noise pollution and their effects both on wildlife and humans. All right, so what are some sources? I think we all can kind of figure out what the sources are, and the fact that they're probably going to be higher in urban areas. Transportation, so cars, trains, airplanes. You know, this is a good example of a highway here with lots of noise pollution, and this wall has been built. It's kind of a sound barrier to the neighborhood on the other side of the wall. Construction, we've all seen construction sites that are particularly noisy, and then just a lot of other domestic and industrial activity that goes on to create kind of this ambient background loud noise throughout our lives. Well, why do we care? Not only does it cause physiological stress and loss of sleep, maybe, but it also can affect your hearing, and you can have hearing loss. But what we're going to focus our attention on right now is the effect on wildlife. So it can also cause stress on these wildlife, but it can also get in the way of the sounds that they use for communication or for hunting. And we'll look at little video clips talking about both of those examples. It could damage their hearing just like it could damage ours, and it could affect their migratory routes. So think about whale migration or bird migration. All right, so I'm going to show you a clip about some bats. So bats use echolocation, a type of sound, to hunt with. So as you watch this experiment, think about how you would design an experiment based on what you learned here. How could you perhaps design an experiment to study the effects of noise pollution on bats?
Bats are nocturnal hunters, and I was really fascinated by sonar, this ability to use sound to navigate in the darkness. And as I learned more about bats, I started being interested in the prey of bats and insects, and that led into studying bat-moth interactions, which is an arms race, a coevolutionary battle that's been going on for more than 60 million years. An amazing aspect of the dynamic battle between bats and moths is that they use sound in the hunt. To find prey, bats rely on echolocation. They produce high-frequency calls and listen to the echoes from their targets to find their position. Having long been on the bat menu, moths have evolved strategies to avoid being eaten. There's a lot of different anti-bat strategies, and the one we're studying here is sound production, ultrasound production above the level of human hearing. They have ears to hear bats coming, and then producing their own ultrasound back to the bats.
We've never had a cool situation there where hunting and avoiding being eaten are all involving sound. Sound is such a critical part of those moths' lives and the bats' lives. Well, we put some noise pollution in there, and how does that affect it? Think about how bats might react to if all of a sudden a fossil fuel extraction or drilling site came into an area, how that might affect the noise pollution in the area and the wildlife around there. And famously, the other place where noise pollution is dangerous is with marine mammals. So there are some clear research that looks at the connections between kind of marine noise pollution and the migratory ability of whales. So as we watch this experiment, or this video, I want you to think again, can you analyze the experiment that they did on the squid? Can you think about what their variables were, how they set up the experiment, what kind of data they collected? So let's look at an experiment on noise pollution with marine organisms.
Whales talk to each other through a complex language of clicks and whistles. These sounds help them to navigate and communicate. Man-made noises like sonar can disrupt this communication and disorientate them.
We know how sensitive people are to whales and dolphins, totem animals, and they were seeing them washed on shore by this human activity for the first time. So this really helped understanding that this noise would have a detrimental effect.
Since this incident, the use of sonar has been associated with a large number of whale strandings around the world. But while beached whales continue to grab the headlines, Michelle was keen to understand if other creatures were experiencing the same fate.
A group of giant squids were found stranded on the beach. The post-mortem analysis didn't show any cause of the death.
What he was about to discover would change scientists' understanding of the effects of ocean noise pollution.
This group of experts realized that a geophysics experiment using a high-energy sound was performed a few days before this event.
Oil prospecting ships had unknowingly disturbed the ecosystem below them.
We decided in our laboratory to recreate this situation, and we found this massive acoustic trauma when we exposed this animal to sound.
Although squid don't have ears, their bodies contain small organs called statocysts, which align with noise-sensitive hairs. In his lab, Michel and his team discovered that even low-intensity sounds destroy these hairs and knock out the squid's balance.
We went through the idea that it was only affecting a few species, the whales and dolphins, to invertebrates and fish, and we're speaking about thousands of species. So we cannot anymore consider the effect of noise as species-specific, but consider it as a global effect to the whole marine environment.
All right, so let's do a little quick check for understanding about what we've talked about today. So this question says, scientists have observed that the health of people living in moderately developed regions, which have developed transportation and industry but lack environmental control measures, is more likely to be affected by urban outdoor pollution than indoor air pollution. Which of the following conclusions can be drawn from the data presented in the graphs? So I'll give you about 30 seconds to take a look at that and pick an answer. All right, so our answer is A. In moderately developed regions such as China and Latin America, an individual's health is more likely to be affected by outdoor than by indoor. All right, let's go to the second question about this, or about the same graph. Which of the following activities would most likely account for the levels of indoor air pollution in sub-Saharan Africa as shown on the graph? And our correct answer is B here. Use of biomass fuels such as sources such as wood and charcoal for cooking. All right, let's take a look at this last question together. It says, over a 3-year period, a city's Environmental Protection Department measured the particulate matter, PM2.5, in a 10 square mile area around one of the city's coal-fired power plants. The annual mean level of PM2.5 measured was 20 micrograms per cubic meter over the 3-year study period. The National Ambient Air Quality Standards for PM2.5 is an annual mean level of 12 micrograms per cubic meter, averaged over 3 years. The city instructs the manager of the power plant to propose a plan to aid the city in meeting the NAAQS for PM2.5 in the area around the power plant over the next 10 years. Which of the following would be the most effective plan for the manager to propose to the city? And you should have put your eyeballs on electrostatic precipitator. That's going to be our best effective measure for particulate matter. All right, so let's try one more time to practice these scientific experimentation skills. So remember, you're going to do things like identifying a hypothesis or a question, identifying research methods, designs, or measures used, describe those things. This part is not obsessed because that's what you would do in class when you actually collect data yourself. And then maybe explain modifications to an experimental procedure that will alter the results. So let's take a look at this example here. You are the property manager for a large apartment complex. Several residents have reported issues of mold growing in their bathrooms. You know that a lack of ventilation can increase the moisture humidity of indoor air, which is often associated with the growth of mold, and want to determine if you can reduce the moisture content of the air. The local EPA office suggests you try desiccants, which are dehydrating products that absorb moisture out of the air. You want to know how well the desiccant products can reduce humidity levels, which you can measure with a hygrometer. So take about 30 seconds or so and think if you could answer these 5 questions. All right, so if we just look at the scientific question, well, the question is how well these products can reduce the humidity levels. That's our goal here. And there's many different experiments that you could design to accomplish this. I'll describe the one that I thought of. So I thought of taking 4 containers, container A, container B, container C, and container D, sealed containers, and squirting water in there until I got it to about 50% humidity. And I could measure those humidity levels with a hygrometer. So I've got 4 equal containers, equal size, shape, materials, all that. They all have the same level of humidity now. So in container A, I don't put anything in there. There's no desiccant package at all. In B, I put 1 desiccant package. In C, I put 2. And D, I put 3. So that's the experiment that I kind of thought of testing how well these desiccants can reduce the humidity. So if I do that in written form, I said I will set up 4 different sealed containers, each with starting humidity of 50% as measured with the hygrometer. Container A will not have a desiccant package, while containers B, C, and D will have 1, 2, and 3 desiccant packages respectively. I will measure the humidity of each box using the hygrometer once a day for 2 weeks. In terms of what is the independent variable, well, that would be my number of packages. That's the thing that I'm changing. What is resulting from that is the percent humidity. And my control group is clearly container A that contains no desiccant package. So this is an example of how you can look at an issue such as mold and come up with an experiment to try to learn something more about it, especially prevention. All right, so what did we do today? Talked about lots of indoor air pollutants. We talked about how to reduce those air pollutants with things like the scrubbers and the electrostatic precipitators and the vapor recovery systems and the catalytic converter. Then we looked at acid rain and finally noise pollution. And throughout each of those, we tried to practice some part of scientific practice number 4 on experimentation. So that is all of our review for the first 7 units, but we still have next week to go. So here's what we're going to be doing next week. On Monday and Wednesday, you're going to have a full practice exam. Remember, our exams are 2 questions. So on Monday, you're going to have a full practice exam here with us live. We'll give you 2 questions. We'll time it out. Give you the time to answer it just like you would on the regular exam. So that happens on Monday. On Tuesday, we'll go over this question. And then Wednesday, you'll have a whole new chance to practice 2 more questions. And then on Thursday, we'll go over those answers. Okay? So during those discussions, we'll highlight big misconceptions and misunderstandings that have happened in the past. What are the key practices and skills you need to answer those questions? We'll look at those task verbs that we've been looking at all through the course of the review. And then we'll talk about we'll review the testing procedures. So about your exam ID, your exam ticket, your e-ticket, what time to show up for the exam, how do you prepare for it? We'll go over those things as well. And then we'll just give some final tips and suggestions for myself and Ms. Fassler. We're both going to generate some best practice tips for doing both types of the FRQ, the experimental design FRQ and the propose a solution to environmental problems. So hopefully we will see you next week. Thanks for watching and have a good weekend. Bye, everybody.